In this lesson, we want to talk about angles in trigonometry. All right, so let's start out the lesson by talking about some basic definitions. We'll think about the concept of a line segment, and a ray. So let's suppose that we have two distinct points, and here on the screen you'll see that you have a point A and also a point B. So those two distinct points can be used to determine a line. Okay, so you see we've drawn a line through them. We can also use those letters, the A and the B, to name the line if we want. So we could call this line AB like this, or we could also put the AB, and we could put a line on top like this. Now, I want you to notice that you have arrows at each end, okay, and that tells you that the line continues indefinitely in each direction. Now, similarly, you have something known as a line segment. With a line segment, it's just a piece of a line or a part of a line. So notice how you have an endpoint here with A and an endpoint here with B. So here it doesn't continue indefinitely in each direction. It's a finite or countable length from the point A to the point B. So this is your line segment AB, okay? And you can also write it like this. You can put AB with a little line on top, and you're not going to have arrows there. It's another line segment that's put on top of AB. Okay. Lastly, we're going to talk about the concept of a ray. So here you have one endpoint, okay, in this case it's going to be A, and it's going to extend through this point B indefinitely, okay? So we see this arrow here, it tells us that it starts at A and continues through B indefinitely. So this is going to be the ray AB, or you could write AB, and you can do this. All right, so now I want to talk about an angle. And basically an angle consists of two different rays with the same endpoint. So when we talk about the two rays, these are the sides of the angle, and the common endpoint is the vertex of the angle. So if we look at our example here, we have a ray AC. So we have a ray AC. And then we have another ray, which is AB. So another ray, which is AB. So these are going to be the sides for my angle, okay? Additionally, A is the common endpoint, so that's my vertex. Now, if I'm naming the angle, then I can call it angle CAB. You can go in order like that. Or you could go the other way. You could say angle BAC, okay? Or you could just use the letter of the vertex. Now, we can write out angle each time, or you can use this special symbol. So you can use this symbol here, and I could say, okay, this is angle CAB, or it's angle BAC. Okay, notice how A, the vertex, is in the middle each time. And then also I can just use the letter of the vertex. So I can say this is angle A. All right, now associated with every angle is going to be its measure, which is generated by a rotation about the vertex. So the measure will be determined by rotating a ray starting at one side of the angle, which is called the initial side. So let me just highlight that. For in this case, the initial side is here. We'll talk more about the standard position later on in the course. For right now, our initial side is going to be right there, okay? So that's the starting position, and then we rotate to the other position on the other side, which is known as the terminal side, which in this case is right here. So you can imagine that you started with two rays that are on top of each other. So this guy represents this guy in the end, and I know I'm not drawing that perfectly well, but basically you can think about starting here and then just rotating about the vertex to get here. So this is your initial side where the two are on top of each other, and then it rotates to the terminal side where you still have one ray here, or one side, and then another ray up here. Now, when we rotate in a counterclockwise direction, so meaning I start here and I rotate this way, okay, that's how I'm measuring. Well, what happens is I generate a positive angle. Okay, now if I go the other way, if I go clockwise, I'm going to generate a negative angle. We'll talk more about this as we progress through the course, but basically if I started this way and I went that way, okay, now I'm generating a negative angle. Now you could imagine if I started here and I went this way around to generate the same terminal side, okay, well now I would have a positive angle because I'm going counterclockwise for the rotation. Okay, so we'll talk more about this as we progress. All right. So when working with angles, we're often going to measure our angle using the degree. Okay, so this is a unit of measure for us. We'll also see radians here shortly. But for now, when we work with the degree, we assign 360 degrees to one complete rotation of a ray. So in other words, what we're saying here is that the terminal side of the angle will correspond exactly to the initial side when it makes this complete rotation. So you can see this image that we have here, and you can imagine that we started out with two rays that were on top of each other, okay? And then we rotated it completely around. So it's one complete rotation here. And we assign the value to that angle 360 degrees. Okay, so that's one complete rotation. Now, of course, you're going to have a lot of scenarios where you make more than one complete rotation or less than one complete rotation. So if, for example, you made 1 over 360, that amount of a complete rotation, well, we would just take this number in the numerator here, which is 1, and we would say that we have 1 degree in this case, okay? We can also write this using our degree symbol, so we can say it's 1 degree like that. If you had, for example, 5 over 360, okay, that amount of a complete rotation, this would be now 5 degrees, okay, that would be the measure of that angle, and you can, of course, still write it like this, 5 degrees. Now, when we work with angles, we're going to have some terminology that we have to get used to. So the first guy I want to talk about is an acute angle. Okay, so this is where the measure of the angle is greater than 0 degrees, but less than 90 degrees. So you see you have this Greek letter here, theta, and in trigonometry, we often use these Greek letters to represent an unknown angle. So here, this is just some unknown angle. Again, theta here, we'll say that theta is greater than 0 degrees, but less than 90 degrees. So this is an acute angle. Now, we've all seen right angles in our algebra course, especially when you're talking about the Pythagorean formula. But a right angle, in case you don't know, you're going to denote this with this special symbol here, okay? And this is where your angle is exactly 90 degrees. Okay, so theta here we can say is exactly 90 degrees. So next we want to talk about something known as an obtuse angle. So this is an angle that is greater than 90 degrees, but less than 180 degrees. So here we can say that theta is greater than 90 degrees, okay, the right angle, but strictly less than 180 degrees, which we'll find out in a minute is a straight angle. So for the straight angle, what we're going to have is theta is going to be 180 degrees. And basically what you have here, you can imagine you start out with, again, two rays on top of each other. You make half of a complete rotation. Okay, so this guy ends up right here, okay? And you end up with what looks like a straight line, right? But basically you started with two rays on top of each other, you made half of a complete rotation, and now the two rays are facing away from each other, okay? And in terms of the complete rotation, we know the degree measure is 360 degrees. This is half of a complete rotation, so half of 360 is 180, so that's why theta here is 180 degrees for your straight angle. All right, so let's wrap up the lesson and talk about complementary and supplementary angles. So we'll start with complementary angles, and basically when the sum of the measures of two positive angles is 90 degrees, the angles are known as complementary angles. So here's a typical example. You can see that the bigger angle here, if I started from here and I rotated here, this is a 90-degree angle. Again, this is given to us by this symbol right here, okay? But we have these two smaller angles, and we want to find out their measure. So you have one that's given by this guy right here, 15x plus 12 degrees, and another that's given by this guy right here, the 12x minus 3 degrees. So to find the measure of each angle here, we use the fact that, again, the complementary angles sum to 90 degrees. So I'm going to take this measure here, which is 15x plus 12. I'm going to leave the degrees off for now. Then plus this measure here, which is 12x minus 3. I'm going to set this sum equal to 90 for 90 degrees. So we're going to solve this, and basically 15x plus 12x is 27x. Then 12 minus 3 would be 9, and this equals 90. So what I'm going to do now is just subtract 9 away from each side of the equation. And of course, this is going to cancel. We get 27x is equal to 81. Divide both sides by 27, and you're going to get that x is equal to 3. So let me write that up here. We'll say that x is equal to 3. So we're not done. We need to find the measure of each angle here. And x equals 3 just tells you what you need to plug in. Okay, so don't stop there. So we would have 15 times this 3 plus 12. Okay, so 15 times 3 is 45. 45 plus 12 is 57. So the measure here that you're looking for is 57 degrees. Okay. Then the other guy is going to be 12x minus 3. So 12 times 3 and then minus 3. 12 times 3 is 36. 36 minus 3 is 33. So the measure of this angle here is 33 degrees. And you can see that the measure of 57 degrees plus the measure of 33 degrees gives you a measure of 90 degrees, which again is the measure of the bigger angle. Okay, so now let's talk about supplementary angles. So we already know that a straight angle here, so if I started here and I rotated, again, this is a half of a rotation. This forms a straight angle. It's 180 degrees, okay? Half of 360 degrees, 180 degrees. That's how you remember your straight angle. So when the sum of the measures of two positive angles is 180 degrees, the angles are known as supplementary angles. So this example is basically the same in terms of how you set things up. You have this angle here that's 9x minus 5 degrees, so 9x minus 5. You have this angle over here, which is 5x plus 3 degrees. So I just put those two as a sum. So 9x minus 5 plus 5x plus 3. So I've got my sum going there. And I set it equal to 180 for 180 degrees. Again, that is the full angle, right? If I consider this all the way from here to here, it's 180 degrees. And so what we do here is we just solve. 9x plus 5x is going to be 14x. Negative 5 plus 3 is, of course, negative 2. So this equals 180. Let's go ahead and add 2 to both sides of the equation. We get 14x is equal to 182. We can divide both sides by 14 and find that x is equal to 13. So x is 13. Again, don't just put that and stop. You need to plug in to find out your measures, okay? So 9 times 13 minus 5. 9 times 13 is 117, minus 5 is 112. So this guy is 112 degrees, okay? And then 5 times 13 is 65. Let me write that out. So 5 times 13 is 65, plus 3 is going to be 68, okay? So this would be 68 degrees. So again, if you look at the sum of 68 degrees and 112 degrees, you get your 180 degrees, which once again is the total measure of this angle, right? So if we think about the whole angle, including this smaller angle and the other smaller angle, is 180 degrees. So we would expect that 68 degrees plus 112 degrees to sum to 180 degrees, and in fact, it does. In this lesson, we want to talk about angle measures in degrees, minutes, and seconds. All right. In our last lesson, we talked about some of the basics that are involved with angles. And we also learned about the unit of measure known as the degree. It's how we can measure our angles. We also have radians, but we'll talk about that later on. So we learned that a complete rotation, or one complete rotation, is assigned the value of 360 degrees in terms of the measure of the angle that is produced. So let's say I started with two rays that were on top of each other. Again, I take this ray and I rotate it completely around, okay, completely around. So what happens is the measure of that angle is assigned a value of 360 degrees. Now, if I think about this in terms of 1 over 360, so let's say I made that amount of a complete rotation, well, this is now going to be 1 degree. If I made 5 over 360, that amount of a complete rotation, that's 5 degrees, so on and so forth. Now, what happens when we need to measure an angle where the amount of the rotation is less than a degree? So it's a portion of a degree, a part of a degree, a fractional amount of a degree. Well, what we're going to turn to here is going to be minutes and seconds. So this is pretty easy to work with. Basically, you start with the fact that if you have 1 degree and you divide it by 60, this produces a unit known as the minute. Okay, so this is going to give you 1 minute. So this is your notation for the minute. Okay. Now you could also say that 60 minutes is going to give you 1 degree, right? So these two statements are saying the same thing. I can take 1 degree and divide it by 60 and get 1 minute. Or if I multiplied both sides by 60, okay, and cleared the denominator, well, what I'd have is 60 minutes equals 1 degree. Okay, so that's the same thing there. Now, also, we can go smaller. Okay, so we can take our minute, so 1 minute, and we can now divide this by 60, and we're going to get a unit of measure known as the second. Okay, so we're going to say 1 second like this. So that's going to be your notation for that. Okay, and we can also, again, just multiply both sides by 60, and we can say that 1 minute is equal to 60 seconds. Okay, so pretty easy to remember overall. Now, additionally, you can start with 1 second. Okay, and you can say this is equal to, again, 1 minute over 60. And this would be equal to what in terms of degrees? It would be 1 degree divided by, now you'd have 60 times 60, which is 3,600, okay? So we'll use this later on. This is something you probably want to write down in terms of these formulas so that you're going to be good to go when you're doing your homework. All right, let's go ahead and look at the first problem. We're just going to add two of these guys together. It's very simple. You just need to understand how the carrying process works. So let me explain. I'm just going to set this up vertically. You don't have to, but I think it's easier to do it that way. So let's just set this up vertically. So 19 degrees, we got 50, and we got 17 here. So what I have here is 37 degrees, 15 minutes, 45 seconds, plus 19 degrees, 50 minutes, 17 seconds. Okay, so we're adding this together. So we know when we do a vertical addition, since we have a base 10 system, if you get a digit that is 10 or larger, you do a carrying process. Well, here, because of the way we convert things, we're looking for a value of 60 or larger to carry. So when I add 45 plus 17, I get 62, right? So basically, this is saying that I have 62 seconds. But again, if we go back up here, we know that 60 seconds equals 1 minute. So really what I could say is that this is 1 minute and 2 seconds, right? So this is the carrying process you're going to use. You're going to put 2 seconds down here, and you're going to carry this 1 into the next column, okay? Just like if you were doing a vertical addition, it's no different. It's just you're changing the way you think about things because you're using 60 now, okay? So in this one, I've got 1 plus 15 plus 50. So 1 plus 15 is 16, 16 plus 50 is 66. So again, now we have 66 minutes, and again, if we go back, we know that 60 minutes equals 1 degree. So I can say that this is 1 degree and 6 minutes, okay? So I'm going to put my 6 minutes down here. I'm going to carry my 1 degree up and over to the next column. And now I'm good to go. I do 1 plus 37, which is 38, and 38 plus 19, which is going to give me 57, so 57 degrees. So the answer here would be 57 degrees, 6 minutes, and 2 seconds. All right, now let's move on and talk about a subtraction problem. So you're going to find the process very similar to vertical subtraction. So let's just go ahead and set this up. So we have 14 here, degrees, 18 minutes, 30 seconds. We have 9 degrees, 25 minutes, 50 seconds. So put my subtraction sign out here. And what you're going to do is think about the fact that, again, I have 30, I have 50. So I want to subtract here. So what I have to do is borrow, right? And think about the fact that 1 minute is equal to 60 seconds, right? So if I take 1 away from this and make this 17 minutes now, I can take this and convert it into seconds. So I can say 30 seconds plus 60 seconds would be 90 seconds. So I'm just going to put 90 seconds there. I'm just borrowing. Again, just like I do with vertical subtraction, same thing. I've just got to get used to that number of 60, okay? So 90 minus 50 is going to be 40. So this is 40 seconds. Then when I get over to this column here, I've got to do the same thing again. So I've got to borrow. I'm going to borrow here and put this as a 13 degrees. And remember, if I think about 1 degree, it's equal to 60, okay, 60 minutes. So I'm going to add 60 to 17. That's going to give me 77, so 77 minutes. And then 77 minutes minus 25 minutes is going to give me 52 minutes. So now I move into my leftmost column. I have 13 degrees minus 9 degrees. That's just going to be 4 degrees. So my answer here will just be 4 degrees, 52 minutes, and 40 seconds. Okay, let's find the complement and also let's find the supplement of the angle that's given. So we know that complementary angles sum to 90 degrees. We know that supplementary angles sum to 180 degrees. So if you're asked to find the complement of this angle, what I would do is I would subtract 90, okay, minus this 29 degrees, 15 minutes, 6 seconds. So of course you need to borrow here, so you can just go ahead and write this as 89 degrees, okay? And I'll put this as 60 minutes. You need to borrow again, so let's just write this as 59 minutes. And let's just go ahead and write this as 60 seconds. So all I did was I took the 90 and I borrowed again so we can do our subtraction, okay? So we go through now, we're good to go. 60 minus 6 is 54. So this is 54 seconds. 59 minus 15 is 44. So this is 44 minutes. And then 89 minus 29 is going to be 60. So this is 60 degrees. So the complement of this angle here is going to be 60 degrees, 44 minutes, 54 seconds. Now, similarly, you can erase this part. And up here, what I'm going to do is I'm going to put 179. Nothing else will change. Because if I put 180 there, again, I'd have to borrow and then borrow again. Okay, so this is how you would set it up. And once you've done this, it's very easy. You just go through and say, okay, well, 60 minus 6, we know that's 54, so 54 seconds. 59 minus 15, again, we know that's 44, so 44 minutes. And then 179 minus 29 is 150, so 150 degrees there. So the supplement of this angle would be 150 degrees, 44 minutes, 54 seconds. All right, so now what we want to do is go from this decimal form here, this 114.09 degrees, to degrees, minutes, and seconds. So this is a pretty common task and very easy to do. So in the end, you want something that looks like this. You're going to have degrees, you're going to have minutes, and you're going to have seconds, okay? So you take the part in front of the decimal point, the 114, that whole number part, and just put it right here for your degree. Okay, so it's 114 degrees. You're good to go with that. Now, you move on to the part after the decimal point. So this 0.09. So 0.09 degrees is what I have left over after I fill that out. Now you want to convert this into minutes first, okay? So remember, 1 degree is equal to 60 minutes. So to get this in terms of minutes, I need to multiply by 60, okay? So I would take this, and let me just erase this. We don't need this. So times 60. This would give me 5.4, okay? 5.4. Now, this now is in terms of minutes. So this is in terms of minutes. I'm going to take the whole number part again, and I'm going to just drag that up here. So I'm going to put 5 here, and now I'm going to say that I have 0.4 minutes. So remember, when you think about it, you have 1 minute is equal to 60 seconds, okay? So I'm just going to multiply this now, this 0.4, by 60 to get it in terms of seconds, and this is going to give me a value of 24, okay? So when we convert this over, what we end up with is 114.09 degrees is 114 degrees, 5 minutes, 24 seconds. And if you have a TI-83 or a TI-84, it will actually do this conversion for you. You want to type this number out first. Then you want to key up your angle button, which is usually second and then angle. And you want to go down to the DMS for degrees, minutes, and seconds. When you hit that, it's going to give you this out as an output. Okay, so that's another way to do it if you want to use your calculator. All right, so to wrap up the lesson, we want to look at this 119 degrees, 5 minutes, and 15 seconds. And we want to put this into a decimal form. So how can we do this? Well, we're going to start with this 119 here, and then put a decimal point. And we want to think about the 5 minutes, how can we convert that? And the 15 seconds, how can we convert that? Well, I want you to remember that, again, when we think about it, 1 degree is equal to 60, okay, 60 minutes. But also we said that 1 degree divided by 60 was equal to 1 minute, okay? So if I have 5 minutes, okay, if I have 5 minutes, just think about the fact that that would be 5 degrees divided by 60. Okay, so I would say that I could divide this by 60, okay, and I can get this in terms of degrees. Well, 5 divided by 60 is going to be 1 over 12, but I'm going to reduce this in a minute because I'll talk about this further. You're going to end up with this nasty repeating decimal. So just leave this alone for right now. All right, so to get this part in terms of degrees, remember I told you in the beginning that basically if you had 1 second, okay, it was equal to 1 minute divided by 60, okay? And 1 minute divided by 60, we could say is 1 degree divided by 3600, okay? So to get this in terms of degrees, we need to divide by 3600. So let's erase this. So let's erase this and divide by 3600. Okay, so at this point, you would really be adding these two amounts together, and basically from those amounts, you would get a decimal that you can put on here. Now, in a lot of cases, you're going to get a nasty repeating decimal for each of them. It doesn't happen all the time. Sometimes it works out nicely. But my suggestion to kind of limit that is to just get a common denominator going. So I'm just going to multiply this by 60 over 60. This is going to be 300 plus 15 over 3600. And this is going to be 315 over 3600, okay? And this is going to work out to a nice decimal for us, which is 0.0875. So 0.0875, and this is in terms of degrees. So not bad overall, just a lot of things to remember in terms of what the conversion is. Okay, once you kind of have that memorized, it's very, very easy to do. And a lot of times nowadays, you can just do this on your calculator. In this lesson, we want to talk about angles in standard position. And also we want to talk about coterminal angles. All right, so an angle is in what we call standard position if its vertex is at the origin and its initial side lies on the positive x-axis. So that's all it is. That's the whole definition. So in this example here, you see we have a little 35-degree angle. And we can see that our vertex is at the origin, okay? And we can see our initial side is on the positive x-axis. So this guy is in standard position. Now, additionally, when we have an angle that's in what we call standard position, it's said to lie in the quadrant where the terminal side lies. So in this case, my terminal side lies in quadrant 1, okay? So this guy would lie in quadrant 1. Now, additionally, you remember that these guys go counterclockwise. So this is quadrant 2. Okay, so if you had an obtuse angle, you'd be in quadrant 2. If you had an angle that was greater than 180 degrees but less than 270 degrees, you'd be in quadrant 3. And then if you had one that was greater than 270 degrees and less than 360 degrees, you'd be in quadrant 4. Okay. Now, something to keep in mind, you might get an angle whose measure is some multiple of 90 degrees. So it could be 90 degrees, 180 degrees, 270 degrees, 360 degrees, so on and so forth. Well, in this case, we have something known as a quadrantal angle. Okay, so you will not be in any quadrant. Okay, so that might be a question for you on your test. So another little quick example of this, we have another angle that's going to be in standard position. So again, the vertex is at the origin. The initial side is on the positive x-axis. This guy is a 160-degree angle. So it's an obtuse angle, and it's going to lie in quadrant 2, right? Because that's where its terminal side is. Okay. So let's talk a little bit about getting an angle measure that's larger than 360 degrees. We already know that the complete rotation, or one complete rotation of a ray, represents an angle whose measure is 360 degrees. So we've seen this in pretty much every video at this point. So we have two rays on top of each other. If I rotate this guy completely around, so one complete rotation, that angle measures 360 degrees. And let me put 360 degrees there. And basically, if we keep going, we can generate angle measures that are greater than 360 degrees. So as an example here, you can see that we have a 450-degree angle. So a 450-degree angle. And we generate this by making one complete rotation. So one complete rotation, so to right there, okay, where the terminal side would be on top of the initial side. And then we keep going another 90 degrees. So you'll notice how this looks like a right angle or a 90-degree angle, but basically we show here that we made one full rotation plus we went another 90 degrees. So to get this 450 degrees, we take the 360-degree angle, again from one complete rotation, and we add to that 90 degrees. We know from here to here is 90 degrees because this is a right angle. And so we add those two amounts together and we get 450 degrees. Okay, so that's where this guy comes from. All right, so now let's talk about these coterminal angles. So the concept here is that coterminal angles are going to be angles that have the same initial side and also the same terminal side, but differ by amounts of rotation. So the measures are going to be different by some multiple of 360. Okay, and I'll show you how to calculate that in a moment. But basically, if we look at this first example, you see that you have a 55-degree angle and you have a 415-degree angle. So the same initial side, the same terminal side. To get this first 55-degree angle, we start here and we just rotate here. That's all we do. But to get the 415-degree angle, again, you're going to make more than one complete rotation. So you're going to go around once. Okay, so that's 360 degrees. And then plus another 55 degrees. So in other words, you took 360 plus your 55. Okay, let me put my degree symbol in each case. And this gives us the 415 degrees that we see from that angle. Now, to show this without making a little diagram or a little graph, what you could do is just subtract. Okay, so you can either do 415 degrees minus 55 degrees, and that would give you 360 degrees. Or you could go the other way. Okay, it's going to be negative, but it doesn't matter. You're looking for some multiple of 360 degrees. Okay, so if you did 55 degrees minus 415 degrees, you would get negative 360 degrees. Now, let's look at another example of this. In this case, you have one positive angle and one negative angle. So this works as well. You have the same initial side and the same terminal side. So this guy is a negative 45-degree angle, and this guy is a 315-degree angle. So we start here and we go, again, if you're going clockwise, it's a negative angle. So this is a negative 45 degrees. The other one, we're going counterclockwise, so it's positive, and we go in this direction, so we're going around, and this becomes 315 degrees, okay? If you were to subtract the 315 minus a negative 45, so 315 degrees minus a negative 45 degrees, remember, minus a negative is plus a positive, you would get 360 degrees. If you were to subtract negative 45 degrees minus 315 degrees, you would get negative 360 degrees. So again, the way that you subtract is not going to matter. Okay, you're just looking for some multiple of 360 degrees to determine if these guys are coterminal. Again, same initial side, same terminal side. They're going to differ by some multiple of 360 degrees. That's all it is. Let's look at the first example. So we have 110 degrees and 470 degrees. A lot of you can eyeball that and see that the difference between those two would either be, if you did 470 degrees minus 110 degrees, obviously that would be positive 360 degrees. And if you did 110 degrees minus 470 degrees, that would be negative 360 degrees. But again, you're just looking for some multiple of 360 degrees. It could be positive, it could be negative, doesn't matter. Some multiple of 360 degrees. So in this case, we know these guys are coterminal. Okay, for the next one, we have 135 degrees and we have negative 495 degrees. So again, you can just subtract. You could do 135 degrees minus a negative 495 degrees, which would be 135 degrees plus 495 degrees. In this case, that would give you 630 degrees, okay? And if you don't know off the top of your head if that's going to be a multiple of 360 degrees, you just divide by 360 and see if you get a remainder. So if I punch that up on my calculator, I get 1.75. So to say you don't have a remainder, remember, you want something that's either a whole number or an integer, right? You don't want a decimal part or a fraction or something like that, right? You want a whole number or an integer. So because we have 1.75, we know that 630 is not divisible by 360. So this guy is not some multiple of 360. So these guys are not coterminal angles. All right, for the next one, we have 335 degrees and 2,135 degrees. So again, you can just subtract. You can subtract in any order. If I do 2,135 degrees minus 335 degrees, that's going to give me 1,800 degrees, okay? And if I took 1,800 and divided by 360, I would get 5. So we can say that their measures differ by some multiple of 360, okay? So they are going to be coterminal angles. Okay, let's look at another example that you'll see in this section. So they'll tell you to find the coterminal angle that is between 0 degrees and 360 degrees. So for this guy, there's kind of a slow way and a fast way. The slow way is to just keep subtracting or adding, depending on the situation you're given, 360 degrees until you get into the desired range. So I could subtract off 360 degrees and then do it again, and I'd be in the desired range. I can kind of eyeball that and say, okay, well, if I subtract it, take some nice round number. Let's say we take 400. So I take 400 twice. Okay, that's 800. I know if I subtracted 1,020 minus 800, I'd have 220. So I know I'd be about where I need to be. So what I'm going to do is I'm going to take 360 and multiply it by 2. That gives me 720. So this is the amount I want to subtract away from here. Again, it's the same thing as if I subtracted away 360 and then I subtracted away 360 again. Okay, that's all I'm doing. So I'm going to subtract away 1,020 degrees minus 720 degrees. This is going to give me exactly 300 degrees, okay? And we are in the range that we wanted between 0 degrees and 360 degrees. Okay, the last example is negative 596 degrees. Again, if you want to find a coterminal angle where it's between 0 degrees and 360 degrees, in this case, you need to add, because it's a negative, 360 degrees until you get where you need to be. Okay, so I know if I add once, it's not going to be enough. Again, I can just use 400 and say, okay, negative 596 plus 400, just approximating, is going to give me negative 196. So I know I'm not in the range with that, so I'd have to add again. So if I added again, I'd be at 204, okay? And that seems like that's where I want to go. Okay, so what I want to do is say, okay, I need 2 times 360, which again is 720, okay? So I'm going to take negative 596 degrees and add 720 degrees. Of course, what you're going to do there is just subtract, right? So you would do 720 degrees minus 596 degrees, which would give me 124 degrees. right? So in this case, I'd have 124 degrees as my answer. This would be the coterminal angle with this guy, okay? That fits the criteria where it's greater than 0 degrees and less than 360 degrees. In this lesson, we want to talk about angle relationships and similar triangles. All right, for the first example, we're going to look at a problem that involves vertical angles. This is something very simple. Basically, vertical angles are angles opposite of each other where the two lines cross. So you can see here we have these two lines that cross, and at this intersection point, you have angles 1 and 3 that are across from each other. Okay, so those are vertical angles. And then you also have angles 4 and 2 that are across from each other. So those are vertical angles, right? You can show it like this with matching arcs. So I can just do 2 like this here and 2 like this here. And what I'll do is I'll do 1 here and 1 here, okay? So angles 1 and 3 would have the same measure, and angles 4 and 2 will have the same measure, okay? That's a property of vertical angles, just saying that vertical angles are going to have equal measures. If we want to find the measure of angles 1 through 4, what we do is we say, okay, we're given the measure of angle 1, it's 10x plus 35 degrees. We're given the measure of angle 3, it's 20x minus 55 degrees. Okay, well, what we can do is set angle 1, which is again 10x plus 35 degrees, equal to angle 3, which is 20x minus 55 degrees. That's going to give me the value for x, and then I can plug that back in and find out what is angle 1, what is angle 3. So I'm going to go ahead and just subtract, and let me scroll down and get some room. I'll come back up to the diagram in a minute. So I'm going to subtract 20x away from each side of the equation, and let's go ahead and get rid of this. And I'm going to subtract 35 away from each side of the equation. So let's go ahead and get rid of this. And then if I do 10x, okay, 10x minus 20x, that's going to give me negative 10x. And this is equal to negative 55 minus 35 is going to be negative 90. If we just divide both sides by negative 10, we're going to find that x is equal to 9. Okay, so let's erase everything. And if you're on a test or something like this, you just have to plug into one of these because, again, these are vertical angles, so the measure is the same. Okay, so we know that x is 9. And if I plug in, 10 times 9 is 90. 90 plus 35 is going to be 125. Okay, so the measure of angle 1 is 125 degrees. Okay, 125 degrees. And also the measure of angle 3 is 125 degrees as well. Okay, and you could plug in there. And again, if you plugged in a 9, 20 times 9 is 180. 180 minus 55 is 125. Okay, so that's where you get the 125 degrees. Now, the other thing that you would note here is that these guys' angles 1 and 2 are going to be supplementary angles, right? Their measure is going to add up to 180 degrees. If you kind of rotate this, you can see that this guy right here, again, this is a straight line. Okay, this is a straight line. So if I took the measure of angles 1 and 2, let me just do this as a full arc here, okay? This would be 180 degrees, right? It would be a straight angle. So we know that the measure of angle 2 can be found by taking 180, okay, degrees and subtracting away 125 degrees, and that would give us 55 degrees, okay? And again, because angles 2 and 4 are vertical angles, I can just put this as 55 degrees as well. Okay, so our answer for this problem is that we have 125 degrees for the measure of angles 1 and 3, and then 55 degrees for the measure of angles 2 and 4. All right, so let's look at an example that involves a transversal that intersects parallel lines. So we see that 8 angles are formed here. You have 1, 2, 3, 4, 5, 6, 7, 8. Okay, those angles there have certain properties. So the ones I want to draw your attention to, we have interior angles. So you can think about this as being between the parallel lines, or some people say inside of the parallel lines. So those would be the angles 3, 4, 5, and 6. Okay. When we have alternate interior angles, they're going to have equal measure. Okay. So angles 3 and 6, those would have equal measure. And then also, let me kind of change this up. Also, angles 4 and 5 would have equal measures. Okay, so if we look at the alternate exterior angles, so the exterior angles would be, you can think about this as outside of the parallel line, so angles 1 and 2, and then 7 and 8. The alternate exterior angles will have equal measures. Okay, so we can say that would be angles 1 and 8, and then also we can say angles 2 and 7. Okay, so we can use these properties to find out the value for all 8 angles here. So if we start out with the fact that angle 2 has this measure, 11x minus 53 degrees, and angle 8 has this measure, 4x plus 8 degrees, well, let's think about the fact that angles 2 and 7 are alternate exterior angles, right? Alternate exterior angles, so they would have the same measure, okay? So I can really write that the measure of angle 7 is 11x minus 53, okay, degrees. Okay, so we know that angles 7 and 8 together form a straight angle, right? Or an angle that's 180 degrees. So in other words, angles 7 and 8 are supplementary angles. So what I can do here, I can add 11x minus 53 plus 4x plus 8 and set this equal to 180, again for 180 degrees. I can solve for x, I can go back and plug in and find out what is the measurement of each angle 1 through 8, okay? So what I'm going to do here, 11x plus 4x is going to be 15x, and then negative 53 plus 8 is going to give me negative 45, so minus 45, this equals 180. Okay, so if I add 45 to each side of the equation, let me scroll down and get some room going, then what am I going to have? This is going to cancel, and if I do 180 plus 45, I'm going to get 225, and this over here is still 15x. If I divide both sides by 15, I'm going to get that x is equal to 15, okay? So let's erase this, and we're just going to plug in. You can get rid of this, okay? We're going to plug in a 15 starting here. So what is 11 times 15? That's going to be 165. And if I subtract away 53, I get 112. So I know that the measure of this guy is 112 degrees. Again, alternate exterior angles, okay? Alternate exterior angles have the same measure. Okay, so this guy, 2 and 7, have the same measure. So this is 112 degrees here. Remember that vertical angles have the same measure. So that means that 7 and 6 have the same measure. Okay, so this is 112 degrees. 2 and 3 have the same measure, so this is 112 degrees. Okay, so at this point, you know 4 of your angles. And again, you can figure out the rest. You can plug in here if you want. You can plug the 15 in and do it that way. Or you can just take 180 and subtract away 112 and get 68 and fill out the rest, right? Because again, if I plugged in a 15 there, 4 times 15 is 60. 60 plus 8 is 68, so this is 68 degrees. Or again, you can use the fact that 7 and 8 are supplementary angles, so you can subtract 180 minus 112 to get the 68 as well. Now again, 8 and 1 are alternate exterior angles, so they have the same measure. And then again, you can also say that 1 and 4 are vertical angles, so they have the same measure. And 8 and 5 are vertical angles, so they have the same measure. Okay, and there's lots of different ways to go about getting these values, but you can see that for angles 1, 4, 5, and 8, the measure of the angle is 68 degrees. And then for angles 2, 3, 6, and 7, the measure is going to be 112 degrees. All right, so let's look at some examples now that involve triangles. So what you need to know here is that the sum of the measures of the angles for any triangle is going to be 180 degrees. So with this example here, we're given angles 1, 2, and 3. And the measure of angle 1 is 6x plus 1 degrees. The measure of angle 2 is 10x minus 56 degrees. And the measure of angle 3 is given, it's 43 degrees. So all we really need to do is set these guys as a sum, and it will be equal to 180 degrees, okay? So if we set up a sum here, so we'd say 6x plus 1 plus 10x minus 56, then plus 43, and this will be equal to, let me drag this down because I'm going to run out of room here. And let me just get some room going. So this will be equal to 180, okay? And we just solve for x, very simple. So 6x plus 10x is 16x. 1 minus 56 is going to be negative 55. Then negative 55 plus 43 is going to be negative 12. So I'll put minus 12 here. This equals 180. If we add 12 to both sides of the equation, we're going to get that 16x is equal to 192. You get some room going here. To finish things off, I'm going to divide both sides by 16 and get that x is equal to 12. So x is 12 here. So let me erase all this. So we said that x was 12. So for angle 1, if I plug in a 12 there, 6 times 12 is 72. 72 plus 1 is 73. So the measure of angle 1 is 73 degrees. Okay, and you can put it here as well. This is 73 degrees. For the measure of angle 2, it's going to be 10 times 12, which is 120, minus 56, which is going to be 64. Okay, so this will be 64 degrees. And I'll write that in here. This is 64 degrees. We're already given the fact that this is 43 degrees. And again, if you sum these amounts, you're going to get 180 degrees. All right, for the next two problems, we're going to see typical examples where we're dealing with similar triangles. So hopefully you remember this from geometry, but essentially if you have similar triangles, then corresponding angles must have the same measure, okay? Then secondly, corresponding sides must be proportional. So that means the ratios of their corresponding sides must be equal, okay? So for the first problem, we're going to deal with the statement that says that corresponding angles must have the same measure. Okay, so we have these two similar triangles, and I'm just going to call this first one triangle ABC. So I'll say triangle ABC is similar to triangle DEF. Now, what you want to do is match up the corresponding angles for this problem. You'll notice that the corresponding angles have matching arcs. Okay, so we have one arc here and one arc here. So angle A corresponds to angle D. And then you have two arcs here and two arcs here. So angle B corresponds to angle E. And then you have three arcs here and three arcs here. So angle C corresponds to angle F. Now, as we just said, corresponding angles, if you have similar triangles, they must have the same measure. So what that tells me is that if I know the measure of angle F is 144 degrees, then I also know the measure of angle C is going to be 144 degrees as well. If I know that the measure of angle A is 18 degrees, that tells me that the measure of angle D is 18 degrees as well. Now, what I don't know here is the measure of angle B and the measure of angle E. So let me fill out this guy right here. I'll just put E and I'll put a question mark. And for this one, I'll put B and put a question mark. Now, how can we figure this out? Well, remember, when we think about the sum of the measures of the angles of any triangle, it's going to be 180 degrees. So what I could do is take 180 degrees and subtract away the sum. So in each case, it's 18 degrees plus 144 degrees. So this sum represents the angle measures for two angles, and 180 degrees would be the sum of all three. So if I take this one, subtract away the sum of the two, I'm going to get the missing one. So let's put this as equal to, so 18 degrees plus 144 degrees, that would be 162 degrees. So this, let me just slide this down, would be 180 degrees minus 162 degrees, which gives me 18 degrees. So if we're trying to find the measure of angle B, it would be 18 degrees. And again, because angle B corresponds to angle E, they're going to have the same measure. So this is 18 degrees as well. So if you wanted to know the angle measure for all of these guys, well, in this bottom triangle, the measure of angle A is 18 degrees. The measure of angle B is 18 degrees as well. And the measure of angle C is 144 degrees. And then in the top triangle, the measure of angle D is 18 degrees. The measure of angle E is 18 degrees. And the measure of angle F is 144 degrees. All right, for the last problem here, let's look at an example with similar triangles where we're asked to find some missing side lengths. So this is a very easy problem to solve. It just deals with proportions. And essentially what you're going to do here is look at these two guys, and generally you're going to be given a statement that says something like triangle ABC is similar to triangle DEF. Now, we already know about finding the corresponding angles. You could do it based on the way that I read the two triangles. So again, I said triangle ABC is similar to triangle DEF. So that tells me that A is going to correspond to D, B is going to correspond to E, and C is going to correspond to F. Or again, you can use those matching arcs. So you have a single arc here and a single arc here. So B and E are going to correspond. You have a triple arc here and a triple arc here. So A and D are going to correspond. And then a double arc here and a double arc here. So C and F are going to correspond. Now, when it comes to side lengths, a lot of times you just have to write things down if you're given a not so easy scenario. Here it's very easy, you can match things up, but sometimes the triangles are flipped all the way around and stuff like that, so it's not so easy. So you might want to write the statement out and say triangle ABC is similar to triangle, in this case, DEF. And then you can just match things up. So I can say this side AB is going to correspond to this side DE. So here's my side AB, here's my side DE, those are corresponding sides. Then I have the side BC that's going to correspond to the side EF. So here's my side BC and my side EF. You can see those are corresponding sides. And then lastly, you can say this side AC is going to correspond to this side DF. So here's my side AC, my side DF. Those are corresponding sides. Now we know if we're working with similar triangles that corresponding angles must be equal, and corresponding sides must be proportional. So again, this just means that the ratios of their corresponding sides must be equal. So let's use that to set up a little proportion. So I know that this side AB corresponds to this side DE. Okay, so what I'm going to do is write the ratio of the length of this side AB to the length of this side DE. So I'm going to set that up as a fraction. I'll just say this is AB, so that's going to denote the length of this side. 2, this will be DE, so that'll be the length of this side. I'm going to say that's equal to the ratio of, let's go ahead and say, the length of the side BC, so the length of the side BC, to the length of the side EF. So the length of the side EF. So let me write that in there. And again, we know that BC and EF are corresponding sides. And I'll also say this is equal to the ratio of the length of the side AC, so that's going to be right here, so AC, to the length of the side DF. So DF is going to be right there. So once you have this set up, I would go through and plug in what you can, and then you're just going to solve for what you don't have, okay? Now, before I even do that, a lot of people are going to ask, why did I choose to put the AB on top and the DE on the bottom here? And it actually doesn't matter. You could flip this, but you have to stay consistent. In this case, I wrote the information from the smaller triangle over the information from the bigger triangle, but I could have also set this up as DE over AB is equal to EF over BC is equal to DF over AC. Okay, so as long as you stay consistent, you're going to be good to go. So I'm just going to keep it like this, and I'm just going to replace what I can. So for the length of this side AB, it's 15. So I'm just going to replace this with 15. For the length of the side DE, it's 30. So I'm going to replace that with 30. Now, 15 over 30 is 1/2. So let's just simplify that and say it's a half. Now, for the length of the side BC, it's 30.5. So let me put that in. And then for the length of the side EF, that's an unknown, right? So we don't know the length of that side. And then for the length of the side AC, that's 24. So this is 24. And for the length of the side DF, that is unknown. Let's grab this real quick. And I'm just going to solve one of these at a time. So I'm going to pick the one on the left and say 1/2 is equal to 30.5. This is over. Again, the EF is the length of the side EF. So cross multiply, and you would get EF is equal to 2 times 30.5 is 61. So the length of the side EF is 61. So you can come back up here and just put that this is 61 right here. Or if you wanted to notate this, you could say EF. This just stands for the length of the side EF. That's going to be 61. Okay, let me put DF here, and we'll come back down. So I'm going to set 24 over DF equal to 1/2. You wouldn't want to set this equal here because you're not going to be able to solve. So I'm going to cross multiply again. So this is DF is equal to 2 times 24 is 48. So the length of that side DF is going to be 48. So coming back up, you can put 48 here and 48 here. In this lesson, we want to talk about the trigonometric functions. All right, so to define our 6 trigonometric functions, we're going to start with an angle in standard position. And we're going to name this guy using the Greek letter theta. So you have your angle theta there. Remember, in standard position, your vertex is at the origin. Your initial side lies on the positive x-axis, so this is your initial side. And then this guy over here is called your terminal side. So what we're going to do from here is we're just going to pick some point, okay, that's not the origin, that lies on the terminal side. So this point that I've chosen here, could be any, but I've chosen this one. This is going to be the point which is -6, 6. So -6, 6. Now for the formulas, you want something generic. So what I've done is I've just labeled this as point P with the coordinates x, y. Of course, you can fill that in with whatever you have. Here we have -6 for x and +6 for y. Now, additionally, what we need to do to get started is we need to know about something called r, okay? So r is just going to take the place of d in the distance formula. So you remember that the distance formula, the distance between 2 points in the coordinate plane, is equal to the square root of, you have your x sub 2 minus x sub 1 quantity squared, plus you have your y sub 2 minus y sub 1 quantity squared, okay? So look at what we've done here. We have this point, again, generically, x, y are the coordinates. And we have this guy right here, which is the origin. Most books will call this the point O, okay, for origin. I'm just going to call it the point L because I don't want you to get confused with the coordinates there, 0 and 0, okay? It looks too similar. So point L here, 0, 0 is my origin. I also have another point here to form a right triangle, okay, which is point Q, which has the coordinates x, right, because it's got the same x location, and then 0, right, because it's on the x axis, so x, 0. So we can see that we can form a right triangle, and obviously you could use the Pythagorean formula to find the distance from point P to point L, or the origin, or you could just plug into the distance formula, which is much easier. Now what we're going to do is we're going to replace the D with an R, okay, and I'll explain why that occurs in a future lesson. Let's get to the unit circle first. I want to just keep this simple. Additionally, since we're working with a point that is 0, 0, I can replace this with a 0 and this with a 0, okay? And now I no longer have an x sub 1 and an x sub 2, or a y sub 1 and a y sub 2, so I can just drop this notation, okay? We know that x minus 0 is x and y minus 0 is y, so I can just really say this is x squared, okay, plus y squared under this radical, okay? So we've made that quite simple now in terms of the definition for R. All right, so let's take a look at the 6 trigonometric functions that we're going to work with. Remember, this R here that you see in these formulas refers to what I just wrote. It's the square root of x squared plus y squared. Now, as we move forward in the course, we'll see different ways to remember this. I know a lot of you think about the SOHCAHTOA, okay, if you've taken trigonometry before. But for right now, we're just going to keep this really, really simple. We'll get to that later on. So the sine of theta is going to be equal to y over r. Then the cosine of theta is going to be equal to x over r. Then the tangent of theta is going to be equal to y over x, where x is not equal to 0. The cosecant of theta is going to be equal to r over y, where again, y is not equal to 0. The secant of theta is going to be equal to r over x, where x is not equal to 0. And the cotangent of theta is going to be equal to x over y, where y is not equal to 0. All right, so let's go ahead and look at an example. Let's say that we're given the point 9, -9. And basically, it's going to be the terminal side of the angle theta in standard position is going to pass through this point. Again, 9, -9 would be the coordinates. And we want to find the values of the 6 trig functions here. So let's do a quick sketch. A lot of people like to do that to see what's going on. It's not completely necessary because you're just going to be plugging some things in, but just to get an idea of what's going on. So if we highlight this point here, again, this is 9, -9. That's going to be our point. Let's just call it P, okay? And basically what we're looking at is our angle here, theta, okay? So we want to find the 6 trigonometric functions based on this guy. So let's go back up and let's remember that this is our x value. So our x value is going to be 9. Our y value is going to be -9. Just pull it straight from this ordered pair here, okay? So this is your x and this is your y, okay? Make sure you bring the signs along for the ride. Then your r value is what? Remember, this is found by taking the square root of x squared plus y squared. So the square root of x squared, x is 9, 9 squared is 81, plus y squared. Y is -9, -9 squared is also 81. So you could really write this as 2 times 81 to make it a little bit cleaner, okay? Because you know that 81 is a perfect square. The square root of 81 is 9. So you could really say this is 9 times the square root of 2. To find all the trigonometric functions, you're just going to plug in what you're given, okay? That's all it is. So we go back up, and there will be easier ways to remember this. But for right now, we're just going to reference this. So sine of theta is y over r. So sine of theta is y, okay, which is -9, over r, which is 9 times the square root of 2. Okay, well, we know we want to rationalize this denominator. First off, we can simplify this because this would be -1, but we want to rationalize this. So let's multiply the numerator and denominator by the square root of 2. And this would give us what? It would give a negative square root of 2 over 2. Okay, so that would be your sine of theta. So let's erase this and just kind of make this a little bit cleaner. Okay, so we'll bring this down and bring this a little bit over. And so now let's look at the cosine of theta. So this is x over r. So the cosine of theta, okay, so this is x over r, x is 9, and again, r is 9 times square root of 2. And basically, you're going to get the same thing as this. When you rationalize, it would just be positive, okay? So you would cancel this with this and get a 1 here, and you'd multiply the numerator and denominator by the square root of 2. And essentially, you would have what? You'd have the square root of 2 over 2. So this is the square root of 2. over 2. Okay, so the next one is the tangent of theta. Okay, so y over x. So the tangent of theta. Okay, so what is y? That's -9. What is x? That's +9. So that would be -1. All right, so next we have these guys that we can find by just flipping things. Okay, so we know that the cosecant of theta can be found by flipping the sine of theta. Okay, because this is r over y, this is y over r. So all I want to do for the cosecant of theta is just flip this guy. Okay, so I would have 2 over the negative square root of 2. And if you're smart, before you rationalize that guy, you'll go ahead and flip it, right? Because now we have to rationalize again. So I'm going to multiply this by the square root of 2 over the square root of 2. And that would give me what? You have a negative out in front. 2 times the square root of 2 over this would be 2. And you can cancel. This would cancel with this. And you're just left with the negative square root of 2. Okay, so the negative square root of 2. So then we go back and we see that the secant of theta is r over x. So I'm just flipping the cosine of theta. And again, the only thing that was different between this one and this one is the sine. So I know that the secant of theta, okay, the secant of theta is going to be equal to the square root of 2. Again, you can go through this on your own. You would flip this, and let's just do it real quick so that nobody's confused. It's 2 over the square root of 2, and you multiply this by the square root of 2 over the square root of 2. And so what do you get? You get a 2 down here, okay? That's going to now cancel with this 2 up here. You're left with just the square root of 2, okay? So that's how we got that. Now, the last one is the cotangent of theta, and that is found by flipping the tangent of theta, okay? In this case, the tangent of theta was -1. So if you think about it, you really say that's -1 over 1. Flip it, you still have 1 over -1, which is still -1. So my cotangent of theta will be -1 as well. All right, so let's look at another example. We're going to change things up just a little bit. So you might also be asked to find the trigonometric function values of an angle when we know the equation of the line that coincides with the terminal ray. So I want you to think for a second. We all know that the equation of a line in standard form that passes through the origin looks like this. So it's something ax plus by equals 0. So for example, this x minus y equals 0, if I didn't consider this restriction, that would be a line that passes through the origin, okay? But what we're going to do here is we're going to restrict the x values to either be x is less than or equal to 0, or x is greater than or equal to 0, okay? And what we're going to get is a ray with an endpoint at the origin. Okay, so let's look at an example of this down here, okay? And what you see is that we have x minus y is equal to 0, okay? That line would be drawn if I extended it past this point. Let me kind of highlight this in a different color. If I extended it past this point, 0, 0. But we're going to restrict the x values to be greater than or equal to 0, so we're only going this way. So this is the endpoint, and we go this way. So this is your terminal side, okay? So you might see this as well. All you need to do is pick a point that's not the origin. So in this case, I've picked the point 3, 3, okay? And one way you can do that, if you haven't drawn this guy, you can just pick an x value that lies in this range. Again, don't pick 0. So let's say you chose 3. Plug in a 3 for x. So you know that x is 3. Solve for the unknown y. What's it going to be? In this case, you can eyeball it and see it's going to be 3 as well. But again, if you had to solve, you would just say, okay, 3 minus y equals 0. Let me go ahead and add y to both sides of the equation, and this would cancel, and I get 3 is equal to y. Okay, so x is 3, y is 3. And this is going to make it really easy for us to crank out those 6 trigonometric functions. So what I'm going to do here is go through them more quickly. So let's just write them out. So we have sine of theta, and this is equal to our y value over our r value, and we'll get r in a minute. Then we have our cosine of theta, okay? So this guy is going to be the x over the r, okay? Then you have your, let me slide this down a little bit, so it went a little too far over. So we have the tangent of theta. This is going to be equal to your y over your x. Now we can crank this one out right now because x is 3 and y is 3. Let me label this. This is x, this is y. So 3 over 3 we know would be 1. So let's just put that down right now. Okay, then we know that the cosecant of theta, okay, the cosecant of theta is found by just flipping this guy. So it's going to be r over y. Then the secant of theta, okay, the secant of theta is found by flipping this guy. So it's r over x. And then the cotangent of theta is found by flipping this guy. In this case, you flip 1, right? If you had 1 over 1 and you flipped it, you still have 1 over 1. So it's just 1. So what is r in this case? Well, you would have, let's scroll down and get some room going. So r is equal to the square root of x squared plus y squared. Okay, so x is 3, y is 3. 3 squared is 9. So you'd have 9 plus 9 or 18, right? So 18 is 9 times 2. 9 is a perfect square. It's 3 times 3. So pull that out and you'd say this is 3 times the square root of 2. Okay, so what I'll do is everywhere there's an r, I'll just replace it with 3 times square root of 2. So 3 times square root of 2 and 3 times square root of 2. And you can do it here as well. But what's going to happen is we're going to crank these out really quickly because these are going to be the same and these are going to be the same. Okay, because we have the same x and y value. So x and y, as I just said, are the same. So I'm going to put a 3 here and a 3 here. And you can put a 3 here and a 3 here. Okay. And very quickly, we can see that this cancels and this cancels. So this is going to be the square root of 2 in each case, okay? And we can write that more cleanly, square root of 2. And let's write that more cleanly, square root of 2. And in this case, we need to rationalize, right? So we'd have 1 over the square root of 2. And if I multiply by the square root of 2 over the square root of 2, well, down here I would have 2, okay? And up here I would have the square root of 2. So let's write this as the square root of 2 over 2. And this is the same, right? So this is the square root of 2 over 2. All right, so these were more simple examples. As we progress, we'll see things that are much more challenging. In this lesson, we want to talk about reciprocal identities, signs of trigonometric function values, and also how to find missing function values when we're given one value in the quadrant of the angle. All right, so let's begin our lesson by talking about the reciprocal identities. So in the last section, we talked about the 6 trigonometric functions. We found that some of these functions are reciprocals of each other. So keep in mind when we use the value of r, okay, r by definition is equal to the square root of x squared plus y squared. Okay, and we talked about that in the last video. So we see that sine of theta is equal to y divided by r, okay? And then cosecant of theta is equal to r divided by y, and then in this case, y is not equal to 0. We don't have to have that restriction for r there because r is always going to be a positive number, okay? But we do need it here because y could be 0. So these guys, the sine of theta and the cosecant of theta are reciprocals. So if you know one, you automatically know the other by just flipping the fraction, okay? Then the same thing goes when we look at cosine of theta, which is x over r, and secant of theta, which is r over x. Again, x is not equal to 0 here. Then again, when we look at the tangent of theta, which is y over x is not 0, and the cotangent of theta, which is x over y is not equal to 0, those guys are reciprocals of each other as well. So in your book, when you're talking about the reciprocal identities, let me erase this real quick, they'll write them in a specific way. So we can say that the sine of theta, okay, is equal to 1 over the cosecant of theta, okay? Then you could also say the cosecant of theta is equal to 1 over the sine of theta. Remember, if you have 1 divided by something, okay, all you're doing is you're ending up taking the reciprocal. So if I had 1 divided by y over r, you could really say this is 1 over 1 times the reciprocal of this guy, so r over y. So this ends up being r over y. Okay, so that's all that is. It's just fancy notation. So let's erase this real quick and let's keep going. So we have the sine of theta is 1 over the cosecant of theta. The cosecant of theta is 1 over the sine of theta. Then you say the cosine of theta is equal to 1 over the secant of theta. Okay, and then the secant of theta, again, it's just 1 over the cosine of theta. Let's write these down here. So the tangent of theta is equal to 1 over the cotangent of theta. And of course, lastly, the cotangent of theta is going to be equal to 1 over the tangent of theta. Okay, so that's all this is. It's not very complicated when you see this in your book, the topic of reciprocal identities. You take the two guys that are reciprocals, okay? One will be over here, one will be in the denominator. You can switch the positions again. The sine of theta and the cosecant of theta, those guys are reciprocals. So the sine of theta is equal to 1 over the cosecant of theta. Similarly, the cosecant of theta is equal to 1 over the sine of theta. And you see the same thing with the cosine of theta and the secant of theta, and with the tangent of theta and the cotangent of theta. So let's look at a quick example of this. So we have that the secant of theta is equal to 9/2 or 9/2. What is the cosine of theta? Well, again, the secant of theta and the cosine of theta, those guys are reciprocals of each other. So if this guy is 9/2, all I have to do is flip it and it would give me 2/9. All right, let's take a look at another example. So here we have the sine of theta is equal to the negative of the square root of 6/3. What's the cosecant of theta? Again, these guys are reciprocals. So I can just flip them and say this is 3 over the negative square root of 6, okay? And what I'm going to do is I'm just going to put my negative out in front, and then I'm going to multiply the numerator and denominator by the square root of 6, so I can rationalize the denominator. So this will be equal to the negative of, we'll have square root of 6 times square root of 6 is going to be 6, and you'll have 3 times square root of 6 up here in the numerator. Of course, you can cancel. This would cancel with this. Each is divisible by 3. So this would just be 1, so you can just get rid of it. And 6 divided by 3 is 2. So your final answer here would be the negative of the square root of 6/2. All right, let's talk about the signs of the trigonometric function values. So we know that when we defined the trigonometric functions, we gave r as the distance from the origin, or the point 0, 0 to the point x, y. So since this distance is going to be undirected, okay, the value of r is always going to be positive. So if you look at something like sine of theta, okay, we know that this is defined as y over r, okay? So since r is always positive, we think about the sign coming from just whether or not y is positive or negative. So if you look at your coordinate plane, remember there's 4 quadrants. In the first quadrant, you have the x and y values that are positive. In the second quadrant, the x values are negative, the y values are positive. In the third quadrant, both the x and y values are negative. And in the fourth quadrant, the x value is positive, the y value is negative. Okay, so where is y negative? It's negative in quadrants 3 and 4. So that means if I'm in quadrant 3 or 4, the sine of theta is going to be negative because r is always positive, right? You would end up with a negative over a positive, which gives me a negative. Okay, and I should have put a negative there. But if you look at this little table I have up here, this summarizes everything for you. In the first quadrant, where x and y values are positive, all your 6 trigonometric functions are positive. In the second quadrant, where x is less than 0 and y is greater than 0, your sine of theta is going to be positive, and then the reciprocal, the cosecant of theta is going to be positive as well. As we move into the third quadrant, where again x and y values are both negative, you get just that tangent of theta and cotangent of theta. Again, those guys are reciprocals. Those guys are positive, everything else is negative. And then in the fourth quadrant, where x values are positive and y values are negative, you'll see the cosine of theta and also the secant of theta. Again, those guys are reciprocals. Those guys are positive, everything else is negative. So an easy way to remember this, because trying to remember this chart is kind of hard, is a little mnemonic device. All students take calculus. Okay, so just take the first letter from each. So all A, students S, take T and C for calculus. So all students take calculus, and this goes counterclockwise. So this is for quadrant 1, this is for quadrant 2, this is for quadrant 3, and this is for quadrant 4. Okay, so the A just stands for all, so all 6 trigonometric functions in quadrant 1 are going to be positive. The S is for sine, okay? So the sine of theta, okay, is going to be positive, and you know the reciprocal of that will be positive as well. The reciprocal of the sine of theta is going to be the cosecant of theta. So sine of theta and cosecant of theta are positive in quadrant 2. Then in quadrant 3, you have T for tangent of theta, and then also the reciprocal, the cotangent of theta, so those guys are positive, everything else is negative. And then in quadrant 4, you have a C for cosine of theta, and the reciprocal of that is the secant of theta. So again, those two are positive, everything else is negative. All right, so let's use what we just learned to look at a few examples. We're going to identify the quadrant of the angle based on these conditions. So we have that the cosine of theta is greater than 0 and the cosecant of theta is less than 0. Let's turn to our all students take calculus once again. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. The way I look at it is I just say, okay, well, cosine of theta is greater than 0. So where does that occur? It occurs in quadrant 1 and also quadrant 4. Remember, the C is for the cosine of theta, and it tells you that the cosine of theta and the secant of theta are going to be positive, everything else is negative. So let me just write below this that it's quadrant 1 and quadrant 4 that satisfy that condition. Then what satisfies this condition? The cosecant of theta is less than 0. Remember, the cosecant of theta is going to be the reciprocal of the sine of theta. Okay, so the S stands for the sine of theta, and that's in quadrant 2. So we know that in quadrant 1, everything's positive. In quadrant 2, the sine of theta and the cosecant of theta is going to be positive. And everywhere else, so in quadrant 3 and quadrant 4, the sine of theta and the cosecant of theta will be negative. So this condition is met in quadrants 3 and also quadrant 4. Let's just erase this. And now all you want to do is just say, okay, well, which quadrant satisfies both conditions? Okay, in some cases you might have more than one. In this case, we only have one. It's quadrant 4. Okay, so if you wanted to answer this, you could just erase these. Okay, you don't need them anymore. And you could just write out quadrant 4, or a lot of teachers will just let you write the Roman numeral of the quadrant, just say quadrant 4 like that for your answer. Okay, another type of example you might get is to determine the signs of the trigonometric functions of an angle when, again, it's in standard position and has a given measure. Here it's 110 degrees. So this is really easy to do. This is something where you might want to make a little sketch. So if this guy's in standard position, again, this is going to be your initial side. Here's your terminal side. We know that if it was touching, your terminal side was touching the y-axis like this, it would be a right angle, it would be 90 degrees. If it goes a little further than that, but not far enough to where it's touching here, right? If it was touching the x-axis, you'd have a 180 degree angle or a straight angle. So it's in between those two. So we know it would be in quadrant 2, right? This would be your 110 degree angle there. So in quadrant 2, again, all students take calculus. Very easy. The S tells me that it's sine of theta and also the cosecant of theta. So you can say the sine of theta and the cosecant of theta, those guys are going to be positive, okay? And then the other guys are going to be negative. So you might want to write all these out, or you could say all others are negative. Depending on your teacher and what they ask for, let's just go ahead and write them out. We'll say the cosine of theta. We'll say the secant of theta, okay? Those guys are negative. And then we have our tangent of theta and our cotangent of theta. Those guys are negative as well. So only sine of theta and cosecant of theta are positive for this example. All right, another one of these, we have a negative 150 degree angle. Remember, when you have a negative angle and this guy's in standard position, you're rotating clockwise now instead of counterclockwise. So this is negative 150 degrees. Again, you're starting here and you're rotating clockwise. So again, if you rotated this way, okay, and you got to right here, if it's a negative angle, that would be negative 90 degrees. If it's positive, it would be positive 270 degrees. But here it's negative. So this would be negative 90 degrees. This would be negative 180 degrees. So we're between those two. Again, we're going to land in quadrant 3 here. So that's your negative 150 degree angle. So in quadrant 3, again, just do all students take calculus. So in quadrant 3, you have a T for the tangent of theta, and then also the cotangent of theta. Those are going to be positive. Everything else will be negative. So you have your tangent of theta, and also your cotangent of theta. Those guys are positive, and then the rest are negative. So sine of theta and the cosecant of theta, those guys are negative. And then also your cosine of theta and also your secant of theta, okay, those guys are going to be negative as well. So for this example, the only two that are positive are the tangent of theta and the cotangent of theta. All right, to wrap up the lesson, let's look at a very common type of problem. This is where you're given one trigonometric function value, and you're either given the quadrant or you have to figure out what it is based on the information you have. And basically, you want to come up with all 6 trigonometric function values. So here we're told that the secant of theta is 19 over 11, and the sine of theta is less than 0. Okay, so you can start this off in a few different ways, and there's also multiple ways to do it. But based on what we know so far, we know that the secant of theta, is going to be equal to my r value over my x value. Okay, so if this is 19 over 11, then I know that my r value is 19, and I know that my x value is 11. Okay, so that's important. So I know I'm going to need y, and how do I find y? Remember that r, by definition, is the square root of x squared plus y squared. So let's work on this really quickly. Okay, we'll come back up to this in a moment. So let's just paste this in here so we have a lot of room to work. We know that x is 11. 11 squared would be 121. And I know that r is 19. So I can replace this and say that I have 19 is equal to the square root of 121 plus y squared. If I want to get y by itself, I first have to clear this radical. To do that, I'm going to square both sides. Squaring 19 gives me 361. Squaring this side tells me that this would cancel with this, and I'm left with the radicand, which I'm just going to change the order and say this is y squared plus 121. And now to isolate y, because I'm trying to solve for y, okay? So to isolate this, I'm just going to subtract 121 away from each side of the equation. This would be 240 over here. Over here, this is gone. I'm just going to have y squared. So let me erase all of this, and I'm going to also flip the order around and put y squared on the left and 240 on the right. Again, that doesn't matter. That's just a personal preference. What I'm going to do, let me just kind of scooch this down a little bit. I'll just write this over here because we need some room. I'm going to take the square root of this side, and I'm going to go plus or minus the square root of this side. So 240, if you take the square root of that, you can simplify, right? Because 240 is 16 times 15. So I could say this is 16 times 15. Square root of 16 is 4. Okay, so I could just pull that out and say this is 4 times the square root of 15. Okay, but you do have this plus or minus out in front that is a bit problematic here. So we need one y value. It can't be positive 4 times the square root of 15 and then also negative 4 times the square root of 15. You need one or the other. Okay, so let's go back up and let's go ahead and write all the information that we know. So x is equal to 11. We know that r is equal to 19. And right now we know that y is equal to plus or minus 4 times the square root of 15. But we need to get that down to one single value. Okay, and we're going to do that with the use of this guy right here. Okay, so we're told that the sine of theta is less than 0. So where is the sine of theta less than 0? Remember, if you use your all students take calculus. Once again, this is quadrant 1, 2, 3, and 4. Okay, the S is for the sine of theta, and the A is for all. Okay, so in quadrants 1 and 2, the sine of theta is positive. In quadrants 3 and 4, it's negative. Okay, so let's write 3 and 4 here. 3 and 4 here. Okay, and let's think about the secant of theta. Remember, the secant of theta and the cosine of theta, those guys are reciprocals. Okay, the cosine of theta is going to be positive because this guy is positive in quadrants 1 and 4. So quadrants 1 and 4. So again, when you get this, you're looking for what is the quadrant that matches both. Okay, the quadrant that matches both is going to be quadrant 4. All right, so if we know that this guy's in quadrant 4, then what are the y values in quadrant 4? We know, if we go all the way back up here, that in quadrant 4, your y values are negative. Okay, they are negative. You are below the x-axis. So that tells me, because the y values are negative, that I don't want the positive, I want the negative 4 times the square root of 15. Okay, so once you've figured that out, the rest of it is just plugging things in. Okay, knowing your ratios, having those ready, and then plugging in. As we progress, we're going to go through one more lesson, and we'll go through a section where we start talking about the SOHCAHTOA. Okay, and we'll remember this a little bit easier. For right now, we're putting in terms of x, r, and y. Okay, so we have our sine of theta. Let's just start with that. That is the y value over the r value. Then my cosecant of theta, okay, it's the reciprocal of this. So this is the r over the y, okay? And then let me write out the rest. So we have our tangent of theta, This is going to be our y value over our x value. And then our cotangent of theta is going to be the reciprocal of this. So it's x over y. And then our secant of theta, okay, is given to us, but it's r over x, okay, r over x. But in this case, we already know what it is. It's 19 over 11, okay. Then our cosine of theta, okay, is x over r, but again, it's the reciprocal of this guy, so we can just flip this and say it's 11 over 19. Okay, so let's plug some things in, and let's kind of get some room going here. And let's see, so y, and it's a little bit off the screen here, but we'll just go back and forth. So y is negative 4 times the square root of 15. And r, I know you can't see it, but let's scroll back up. It's 19. Okay, so r is 19. So let me just fill that in everywhere. That way we don't have to keep going back and forth. Okay, so those are the only two places we need the 19. Okay, then y, let me fill that in everywhere. So this is negative 4 times the square root of 15. And let me fill that in here. Negative 4 times the square root of 15. And also here, so negative 4 times the square root of 15. And x, let's just scroll up real quick, that's going to be 11. Okay, so we're done with that. So let's go back up here, put 11, and then go up here and put 11. For the cosecant of theta and the cotangent of theta, you need to rationalize the denominator. So for the cosecant of theta, let's just do this down here. I'll make the whole thing negative. I'll say that I have 19 over 4 times the square root of 15. I'll multiply by the square root of 15 over the square root of 15. Square root of 15 times square root of 15 is, of course, 15. Okay, 15 times 4 is 60. Okay, so you really can't do anything further to simplify. So let's just erase this. Scooch this down a little bit so I have more room. I'll put the negative of, you have 19 times the square root of 15 over 60. All right, so that one's done. And now I just need to rationalize this denominator. So I've got 11 over, let's put the negative out in front. We have 4 times square root of 15. So we'll multiply by the square root of 15 over the square root of 15 again. So we have square root of 15 times square root of 15, which is 15. 15 times 4 is 60. So let's erase all this. Put equals. I'll make the whole thing negative. My denominator will be 60. My numerator will just be 11 times the square root of 15. So 11 times the square root of 15, and I'm all done. In this lesson, we want to talk about the Pythagorean and quotient identities. We'll look at the ranges of trigonometric function values, and also we'll see some examples where we're finding missing function values. So before we jump into the lesson, for reference sake, let's go through the 6 trigonometric functions again. I want you guys to remember the way we've defined this. We've said that r is equal to the square root of x squared plus y squared. Okay, so remember that. So I can also say, if I square both sides, that r squared is equal to x squared plus y squared. So we'll be using this in a moment. So I want you to recall that we defined sine of theta as y over r. We defined cosecant of theta as r over y, where y is not allowed to be 0. Now, you'll notice that, again, sine of theta and cosecant of theta, those guys are reciprocals. Remember your reciprocal identities that we talked about in the last lesson. Then we have our cosine of theta, which is x over r. Our secant of theta, which is r over x. X is not 0. Again, these two guys are reciprocals. Then you have your tangent of theta, which is y over x. X is not equal to 0. And your cotangent of theta, which is x over y. Y is not equal to 0. Again, these guys are reciprocals. Now, our first topic of today's lesson is going to be the Pythagorean identities. So you'll usually see these in your book in this exact manner. So sine squared theta plus cosine squared theta equals 1. Your tangent squared theta plus 1 is equal to your secant squared theta. And then 1 plus cotangent squared theta is equal to cosecant squared theta. So how do we get the first one? So we have our sine squared theta plus our cosine squared theta is equal to 1. We'll see other ways to do this when we get to the unit circle. For right now, we're just going to divide everything by r squared, okay, by r squared. And we know that r squared divided by r squared would be 1. So when we look at this guy, we can say this is now going to be x squared over r squared plus y squared over r squared is equal to 1. Okay, so now using the rules of exponents, remember, I have a 2 here and a 2 here as an exponent, and a 2 here and a 2 here as an exponent, so I can pull that outside of a set of parentheses, right, using my power rules. So I can say this is x over r, okay, this amount here would be squared, then plus you have y over r, this guy here would be squared, this equals 1. Well, by definition, we just saw that x over r is cosine of theta, okay, and then y over r is sine of theta. If we go back up, again, sine of theta is y over r, cosine of theta is x over r. So I could replace this guy right here by saying it's cosine of theta being squared. And I could replace this guy, let me just kind of move this down. I could say this is sine of theta being squared, and this equals 1, okay? So I could apply my exponents and use the commutative property to get into this form here. I can write this as cosine squared theta, okay? And I could write this as sine squared theta, okay? And then I could just switch the order because, again, this is just addition. So when you add two things together, the order doesn't matter. So that's how we get to this form right here. So let's look at the other ones. So we have tangent squared theta plus 1 is equal to secant squared theta. So to get this, let me just erase everything. You're just going to divide everything by x squared now. Okay, quite easy. So divide this by x squared, this by x squared, this by x squared. And we know that this guy is going to be 1. All right, so we know we would have 1 plus, you'd have your y, and I'm just going to write this as y over x, this guy squared, because we know we do that step anyway, is equal to r over x, this guy squared. What is y over x? We know that this is the tangent of theta. So we go back up, again, y over x is the tangent of theta. So you can replace that. You can say this is 1 plus the tangent of theta, this guy squared, is equal to, what is r over x? Well, r over x is the secant of theta. Okay, so we go back and we say this is the secant of theta. Let me make that a little bit better. The secant of theta, this guy's being squared. And again, you can apply your exponents and just say this is the tangent squared theta, okay? And this is the secant squared theta, okay? And then the way we had it was tangent squared theta plus 1 is equal to secant squared theta. So all we'd have to do is just rearrange this and say, okay, I have the tangent squared theta plus 1 equals secant squared theta. Let's look at the last one, which is this guy right here. So 1 plus cotangent squared theta equals cosecant squared theta. And to get this one, I'm just going to divide everything by y squared. And again, it's going to be the same trick overall. So now this guy's going to be 1. So I would write this as x over y. This guy would be squared. Plus this would be 1. This equals, you'd have r over y. This guy is squared. Okay. So x over y, we know that's cotangent, right? So cotangent of theta. X over y is the cotangent of theta. So let's go ahead and say we have cotangent of theta. And I'm just going to put cotangent squared of theta. We know it would end up being that anyway. So then plus 1 equals, what's r over y? So r over y is cosecant of theta, okay? So I'm going to say this is cosecant squared of theta, okay? And again, if I go back, all I have to do is switch the order of these two. So I'll just write this as 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so that's where those three guys come from. Not very difficult to derive overall, but something you might see in your book and get a bit confused about. All right, so now let's move on and look at the quotient identities. These are a lot easier to understand. You have sine of theta over cosine of theta gives you the tangent of theta. Remember, sine of theta is y over r, and cosine of theta, if I divide it by that, it's x over r. Well, what do we do here? This is y over r times the reciprocal of this, which is r over x, okay? So the r's cancel and you get y over x, which by definition is the tangent of theta. So the other one is the cosine of theta over the sine of theta gives you the cotangent of theta. Well, before you even do this, remember, the tangent of theta, okay, which is y over x, and the cotangent of theta, which is x over y, those guys are reciprocals. Well, look at what I did here. I just took the reciprocal of just what I was working with. I had sine of theta over cosine of theta. Now I've flipped that. I have cosine of theta over sine of theta. So, of course, I'm going to get the reciprocal of what I got before, which is the cotangent of theta, okay? So now all I would have is x over r divided by y over r. This is x over r times the reciprocal of this, which is r over y, okay? So these cancel and you get x over y, which again is the cotangent of theta. All right, so one last thing before we start doing these problems. In a lot of cases, you need to know the ranges of the 6 trigonometric functions because you'll go to solve a problem and you might get something that's not possible, but you think that it is possible, and we'll see that on the first example. I'll show you exactly what I mean. So when you look at your trig functions, you have this range. When you think about sine of theta and cosine of theta, the value needs to be from -1 to 1, including -1 and 1, but in that range, okay? When you work with tangent of theta and cotangent of theta, it can be any real number, okay? It can be any real number. When you work with the secant of theta or the cosecant of theta, well then you could really say this is just that the absolute value has to be 1 or larger, right? Because you can have from negative infinity up to and including -1, and then also from 1 out to positive infinity, okay? So basically the absolute value needs to be 1 or larger, okay? It can't be less than that. All right, so let's look at our first example here. We're going to use the identities to find cosine of theta and sine of theta, given the fact that the tangent of theta is 7/3 and the sine of theta is less than 0, meaning it's negative. So first and foremost, think about the quadrant you're going to be in. Remember that all students take calculus. So we have our 4 quadrants, 1, 2, 3, I'll put 4 marks there, should be 3. So 3 and then 4, okay? So all students take calculus. All right. We know that T stands for the tangent of theta and also the cotangent of theta, the reciprocal. So it's positive in quadrants 3 and also in quadrant 1, because everything's positive in quadrant 1. Sine of theta is negative, okay, in quadrants 3 and 4, because the S stands for the sine of theta. So we know that we're in quadrant 3 because it meets both criteria, right? It's going to be positive for the tangent of theta and negative for the sine of theta. So we will be in quadrant 3, okay? So keep that in mind when you get stuff to know whether it's positive or negative. Now, the other thing is, and this is a very common mistake, remember we just said that the tangent of theta is equal to the sine of theta over the cosine of theta. So what students do is they say, okay, well, sine is negative, and I know that tangent is positive, so what they'll do is say, okay, well, this is going to be -7 over -3, okay, over -3, and they think they're done with the problem. This is a very common mistake. Why doesn't it work out this way? Remember, the range for sine of theta and cosine of theta is from -1 to 1, including those two numbers. So this is not possible. You can't have a -7 and you can't have a -3. So throw that out, okay? So what we're going to do is we're going to take our Pythagorean identity that includes the tangent of theta, and we're just going to plug into that. So we have the tangent squared of theta, okay, plus 1 equals the secant squared of theta. Okay, so you might be saying, why would we plug into that? We're trying to find cosine of theta and sine of theta. Well, remember, the secant of theta is the reciprocal of the cosine of theta, okay? So if we find the secant of theta, we can flip it, we'll have cosine of theta, okay? And once we've done that, we know that our other identity involves sine of theta and cosine of theta. We can plug into that and figure out our sine of theta. So let's just go ahead and knock this out. We're given that the tangent of theta is 7/3. So you would want to plug in here, okay? But remember, this guy is being squared. So when you plug in here, make sure that you square this guy. It's very important, okay? So we come down here. Once you've plugged in, the rest of this is really, really easy. You're just doing some basic algebra. 7 squared is 49. 3 squared is 9. Then you're going to add 1 to that. So get a common denominator. Let's just say this is 9 over 9, okay? This is equal to secant squared of theta, okay? So let's go down a little bit more. I'm going to flip this around and put this guy on the left. So secant squared of theta is equal to 49 plus 9 is going to give me 58, and this is over 9. Now to get this in the form of secant of theta, okay, what I want to do, since this is being squared, I want to take the square root of each side. Remember, on this side, I want to go plus or minus, okay, the square root of 58 over 9. I'm only going to need one of these. Remember, I'm in quadrant 3. That's what we did that to begin with. I'm in quadrant 3. In quadrant 3, the secant of theta is going to be negative, so throw out the positive one. You just need the negative, okay? That's all you want. So let's scroll down a little bit, and we'll say the secant of theta, okay, is going to be equal to the negative of, this would simplify because the square root of 9 is 3, so I'll say the square root of 58 over 3, okay? So we're not looking for the secant of theta. Of course, we want the cosine of theta. And I know this is a bit tedious, but the cosine of theta is found by flipping this guy. So this is equal to the negative of 3 over the square root of 58. Now, when you have an answer with the square root in the denominator, you typically want to rationalize the denominator. So let's multiply this by the square root of 58 over the square root of 58. And that would give me an answer of the negative of 3 times the square root of 58 over 58. Okay, so that's my cosine of theta. I also wanted to find sine of theta. Okay, so sine of theta, what is that equal to? Remember, sine squared theta plus cosine squared theta is equal to 1. Well, I can plug in for the cosine squared theta. I'm just going to plug in the non-rationalized version here. So I'm going to put negative 3 over square root of 58. Okay, you don't need the rationalized one because this is not the final answer. Let's copy this because we're going to run out of room. Go to a fresh sheet here. And let me erase this. We don't need that. And scroll down a little bit more. So if I square this, let's just go ahead and put sine squared theta plus. If I square this, I'm going to get positive, of course, 9 over 58. And this equals 1. Okay, so all I got to do is subtract this away from each side of the equation. So I'll have sine squared theta is equal to 1 minus 9 over 58. And of course, we just get a common denominator going. So I'm going to say this is 58 over 58. And 58 minus 9 would be 49. So this is 49 over 58. So this is 49 over 58. Okay, so to get sine of theta, remember you're taking the square root of each side. So do you want the positive or the negative square root? Remember, sine of theta is going to be negative in quadrants 3 and 4. We're in quadrant 3, so it's going to be negative. So I want the negative square root of 49 over 58. Okay, let me make that reach all the way. And of course, this is equal to the negative of, you have the square root of 49 is 7, so we'd have 7 up here, over, you'd have the square root of 58. And to make this a little bit cleaner, because again, we want to rationalize the denominator, sine of theta is going to be equal to, you have the negative of 7 times the square root of 58 over 58, right? Because I'm going to multiply this by the square root of 58 over the square root of 58, and I'll be done. So sine of theta is equal to negative of 7 times the square root of 58 over 58. All right, so let's take a look at another example. We want to find sine of theta and tangent of theta, given the fact that the secant of theta is -2 and the cotangent of theta is greater than 0, or you could say positive. So the first thing is, what quadrant are we going to be in? Well, where's the secant of theta negative? It's going to be negative in quadrants 2 and also 3. Okay, and then where is cotangent of theta? Where is that positive? It's positive in quadrants 1 and 3. Okay, so 3 matches both conditions there. So we'll say this is in quadrant 3. Okay, so this is going to be in quadrant 3. So when we look at this, we know that our sine of theta will be negative and our tangent of theta will be positive. Okay, so keep that in mind when you're solving this problem. So the first thing is we're given the secant of theta, it's -2. So let's plug in to this guy. We have the tangent squared theta plus 1 is equal to the secant squared theta. So I'm just going to plug in for this. Remember, it's squared, so it would be -2 squared, -2, both the negative and the 2 being squared. If I did that, that would be +4. So let's just erase this and put 4 in here, okay? I'm going to subtract 1 away from each side of the equation, so this is gone, and this would be a 3. So what you have here is tangent squared theta is equal to 3. If I want to find out what tangent of theta is, I'm going to take the square root of each side. Remember, we already said this guy is going to be positive, so I don't need the plus or minus. I just want the principal square root here. So it's just the principal square root of 3. Okay, so that's my tangent of theta. So now that we know what the tangent of theta is, how can we find the sine of theta? Well, one thing we can do, we can flip this guy. Since the tangent of theta and the cotangent of theta, those guys are reciprocals, I can say my cotangent of theta is just flipping this guy. Remember, if it's not displayed as a fraction, just write it over 1 and then flip it. So you can say this is 1 over the square root of 3. We're not going to rationalize this here because this is not going to be our final answer. So what I'm going to do now is I'm going to plug this in. I'm going to plug this in for our Pythagorean identity where it says 1 plus our cotangent squared theta is equal to cosecant squared theta. Remember, the cosecant of theta and the sine of theta, those guys are reciprocals. So I can plug in here, find out what this is, flip it, okay, and I'll have sine of theta. So let's go through and plug in. We'll have 1 plus, I'm going to plug this guy in here, 1 over square root of 3. And this guy's going to be squared, and this equals my cosecant squared theta, okay? Let's get some room going. And so now if I square this, I'm going to get what? I'm going to get 1 squared is 1. Square root of 3 squared is 3. So this is just 1/3. This is just 1/3. To add this to 1, I'm going to get a common denominator and say this is 3 over 3. So this is basically going to give me 4/3. So 4/3 is equal to, and let me write this in another way. So cosecant squared theta is equal to 4/3. Okay, so to solve for this guy, remember the cosecant in quadrant 3 is going to be negative. So I'm going to take the square root of this side. I'll say the cosecant of theta is equal to, over here I want the negative square root of 4/3. So the cosecant of theta is going to be the negative of, the square root of 4 is 2, and then over the square root of 3. So now let's cut this. We'll go to a fresh sheet, and we'll just paste this in right here. So remember, if I want the sine of theta, I just flip this guy. Okay, so if I flip this guy, I'm going to have the negative of the square root of 3 over 2, and that's my answer. All right, let's look at one that involves the quotient identities. So we have find sine of theta and tangent of theta, given the fact that our cosine of theta is equal to -2 times the square root of 2 over 3, and sine of theta is negative. So cosine of theta is negative here. Where is cosine of theta negative? Well, it's negative in quadrants 2 and 3. Where is sine of theta negative? It's negative in quadrants 3 and 4. So again, we have a situation where we're in quadrant 3. Okay, and it doesn't always work out this way. We had 3 problems today where they're all in quadrant 3, but it's going to vary based on the problem you're given. So we know we're in quadrant 3. From here, we're going to say that we know our sine would be negative, it's given to us, and we know our tangent is going to be positive because we're in quadrant 3. Okay, so how do we find our sine of theta? Well, we can use our Pythagorean identity, the one that says cosine squared theta plus sine squared theta equals 1. And I know this is normally reversed, but I'm writing it this way to give myself some room because I want to plug in here. So I'm going to plug in for cosine theta, okay? So I'm going to say this is negative 2 times the square root of 2 over 3. Remember, this guy is squared. It's so important that you don't forget to square things, okay? So if I square this guy, the negative becomes positive, so you can forget about that. 2 squared is 4. The square root of 2 squared is 2, okay? 4 times 2 would give me 8. And then down there you have 3, which is squared, which is 9. So I have 8/9 plus sine squared theta equals 1. Okay, let me erase this. We're just going to kind of stick around here because I'm going to need some of that information, so I'm going to be going back up. So let me just kind of drag this up a little bit so that we stay right here. Okay, so what I'm going to do now is I'm going to subtract 8/9 away from each side. So I'm just going to erase it from over here. I'm going to write this as 9/9. So I have a common denominator, and then we're going to subtract away that 8/9, okay? 9/9 minus 8/9 is 1/9. Okay, so 1/9. Remember, sine of theta is negative. So if I take the square root over here, I want sine of theta is equal to the negative square root of 1/9. Now, the square root of 1/9 is the square root of 1, which is 1, over the square root of 9, which is 3. So it's 1/3. All right, so this is negative 1/3. Negative 1/3. All right, so let me erase this real quick. I'm just going to drag this over here. And I want to find tangent of theta now, given the fact that I know what cosine of theta is and I know what sine of theta is. Remember, the tangent of theta is defined as the sine of theta divided by the cosine of theta, okay? So what I can do, it's going to be hard to fit this in this limited room I have, but I would have that the tangent of theta, let me just write that over here. So the tangent of theta is equal to, the sine of theta is negative, the negative of 1/3 divided by the cosine of theta, which is the negative of 2 times square root of 2 over 3. So let me just copy this, and we're going to go to another sheet. We'll paste this in here real quick. So this is equal to what? It's equal to the negative of 1/3 times, flip this guy, the negative of 3 over 2 times square root of 2. Of course, the negatives are going to cancel. Forget about those. The 3's are going to cancel. So what I'm left with here is 1 over 2 times square root of 2. Let's rationalize. We're going to multiply by square root of 2 over square root of 2. And this gives us the square root of 2 over, square root of 2 times square root of 2 is 2, 2 times 2 is 4. So square root of 2 over 4 would be your tangent of theta. In this lesson, we want to talk about trigonometric functions of acute angles, and also we'll look at cofunction identities. So previously, we used angles in standard position to define the 6 trigonometric functions. So what we're going to do in this lesson is we're going to define our 6 trigonometric functions as ratios of the lengths of the sides of right triangles. So we're going to kick things off by looking at an acute angle in standard position. This is something we've already seen. So we've seen this diagram before. So this acute angle here, this angle theta, is in standard position, okay? And we've just picked a point on the terminal side. We're going to call it x comma y. That's our point. But again, this has actual coordinates. In this case, it would be 8 comma 8, okay? But we're just going to refer to it as x comma y. Now, generically, we know that this distance from here to here can be represented by just saying the letter y, okay? Because this right here is y, and down here, this coordinate is going to be 0, right? Because we're on the x-axis. So I could take y and subtract away 0, and I would get y. So that's my distance for this vertical leg here of this right triangle that we formed. Then this horizontal distance from here to here, remember this is a coordinate of x, okay? This is a coordinate of x. And this is a coordinate of 0, so really I could do x minus 0 and just say that the distance from there to there, we could say this is x, okay? And then from here to here, let me highlight this. From here to here, we know that is the hypotenuse, right? So we call this r. We call this r, and we'll get more into that as we progress through the course in terms of why we call it r. For right now, we just call it r. okay? So we've already defined the 6 trigonometric functions using these letters, right? So we've said that the sine of theta is y over r. We've said that the cosine of theta is x over r. We've said that the tangent of theta is y over x. And then using the reciprocal identities, we can get the 3 remaining ones. So the cosecant of theta is going to be the reciprocal of this, which is r over y. And keep in mind, if your denominator ends up being 0, okay, it's undefined. So I'm not going to write that, but y can't be 0 there. Then here you would have the secant of theta, okay, and this would be r over x. And then lastly, you'd have your cotangent of theta, which is going to be x over y. Okay, so let's explore a different way to look at this now. So instead of calling this guy y, okay, we're going to refer to it as opposite because it's opposite of this angle here, okay? Now, what you want to pay attention to is where this guy is, because in this case, this is the opposite side. But if I change the angle up, if I was measuring this angle here, well, then the opposite side would now be here. So you got to pay close attention to this. I'll show you some examples where we switch things up and the answers are going to change. So you got to keep in mind where the opposite side is. So this guy is opposite of your angle theta. And then this guy right here is adjacent to it. Okay, and then of course the hypotenuse stays the same. The hypotenuse is always opposite of your right angle, your 90-degree angle. Okay, so what we can do now is say that, okay, since this was y and this was x before and this was r, well, if we have sine of theta, okay, we said before this was y over r. Now we're going to say it's what? Well, y is the opposite, so I'm going to put OPP for opposite, and this again is the measure of that, so the length that you're given. And then you have your r, your hypotenuse. So I'm going to put HYP for hypotenuse. So opposite over hypotenuse, okay? And I'll give you a mnemonic device for this in just a moment, the SOHCAHTOA. So then you have your cosine of theta, okay? This is x over r, or in terms of this, it's the adjacent, okay? The adjacent over the hypotenuse, okay? And then you have your tangent of theta, which is going to be what? It's y over x, which is your opposite, okay, your opposite over your adjacent, And then, of course, you can flip these guys, and you can get your cosecant of theta. So your cosecant of theta, and I'm going to run out of room here. So let me actually copy this real quick. And let's go to a fresh sheet and just paste this in. So we have more room. So then I can say that cosecant of theta, which is the reciprocal of this, is going to be the hypotenuse over the opposite. And then your secant of theta, which is the reciprocal of this, would be your hypotenuse over your adjacent. And then lastly, your cotangent of theta is going to be the adjacent over your opposite. Okay, so how do we remember this? Well, recall when you work with something like the order of operations, you have your PEMDAS, right? Your please excuse my dear Aunt Sally. Well, you have a similar mnemonic device here. It's the SOHCAHTOA, okay? So the SOHCAHTOA, okay? So the S stands for sine, the C stands for cosine, and the T stands for tangent, okay? So this is pretty much what everybody uses to remember these guys. So S for sine, it's the opposite over the hypotenuse, so opposite over hypotenuse. C for cosine, the adjacent over the hypotenuse, so adjacent over hypotenuse. The T for tangent, the opposite over adjacent, so opposite over adjacent. So this is something you want to write down and think about constantly until you have it memorized. It's going to save you a lot of time. And then, of course, if you know your reciprocal identities, it's very easy to get the cosecant, the secant, and the cotangent by just flipping guys. All right, so let's go ahead and take a look at an example. So with this guy right here, we're just going to find the 6 trigonometric functions. So let me just write them out. We want sine of theta, cosine of theta, and let's just do tangent of theta for right now. We know we can get the other 3 by just flipping these guys, okay? So what is sine of theta? Again, let me go back to the SOHCAHTOA, okay? So sine of theta, it's y over r, but let's think about it in terms of this. We're going to say opposite. So opposite over hypotenuse, okay? Cosine of theta, we're going to do adjacent over hypotenuse. And tangent of theta, we're going to do the opposite over the adjacent, okay? So what's the opposite here? What's the hypotenuse? What's the adjacent? So we know that across from the right angle, okay, which is the longest side of a right triangle, is your hypotenuse. Okay, so this is the hypotenuse right here. Okay, and if you're confused about these things when you first start, go ahead and take the time to label things, figure out where everything is. So this guy right here is adjacent. This is your angle here, theta. Okay, and I made that terribly. So this is your angle here, theta. This guy is adjacent to this, okay, or next to it. So this is going to be your adjacent. And then opposite of this, you're going to have this guy right here. So this is your opposite. Once you've figured this out, you're just plugging things in and you're done. Okay, that's all you need to do. So what is the opposite? It's 2. What is the hypotenuse? It's 2 times square root of 5. Well, of course, you want to rationalize the denominator there. Let me just kind of scooch this down a little bit so we have some room. So I'm going to multiply this by square root of 5 over square root of 5. The 2's are going to cancel. So I'm going to have the square root of 5 over square root of 5 times square root of 5 is 5. Okay, so that's my sine of theta. My cosine of theta is the adjacent, okay, which is 4, over the hypotenuse, which is 2 times square root of 5. The 4 and the 2 would cancel to 2 up there. So again, you're just going to multiply by the square root of 5 over the square root of 5. And what does that give me? Well, 2 times square root of 5, 2 times square root of 5 over square root of 5 times square root of 5 is 5. So the last one down here, we have the opposite over the adjacent. So the opposite is 2, the adjacent is 4, so this is 1/2. Now we can flip these guys again and figure out our other one. So let me erase this. All right, so for the cosecant of theta, remember that's the reciprocal of this guy, the sine of theta, okay? So I'm going to use the one before we rationalize the denominator to make it easy. So 2 times square root of 5 over 2. I just took this guy right here, okay, and I flipped it. That's all I'm doing. You can flip this guy too, but then you have to rationalize the denominator again. It's just double work. Okay, so we've already done that. So cancel this with this. You just get the square root of 5. Then the next one, we would have the secant of theta, okay? And that would give me what? The secant of theta would be the reciprocal of your cosine of theta. So again, take the one before we rationalize the denominator. And I'm just going to say this is the square root of 5 over 2. And nothing really else you can do with that. So lastly, I'm going to flip the tangent of theta, okay, to get the cotangent of theta. And so if I flip 1/2, I just get 2 over 1 or 2. All right, so let's look at another example. We're going to have the same right triangle, but now we're going to change the angle. So before, our theta was here, okay, so we were talking about in reference to that angle. Now the angle has changed, okay? So this is our angle now. And so this guy right here now is the adjacent. Okay, so this is the adjacent. And this is still the hypotenuse. That is not going to change because it's always across from the 90-degree angle or the right angle. And now if you look opposite of this, this is going to be this side over here. Okay, so we've got our adjacent, our hypotenuse, and our opposite. So our sine of theta, again, so, S-O-H, so. Sine is opposite over hypotenuse. So what's the opposite? It's 4. What's the hypotenuse? It's 2 times the square root of 5. You do need to rationalize the denominator here. So let me cancel this with this and get a 2 here. Okay, so 2 over the square root of 5. So this is multiplying by the square root of 5 over the square root of 5. And you're going to get 2 times the square root of 5 over 5. Now I want you to notice something. Sine of theta here is the same as cosine of theta here. Okay, we're going to talk more about this in a moment, but I just want you to notice that. All right, so I can flip this guy to get my cosecant of theta. Okay, let's just do that now. And I'm going to start with it in this form, and I'm going to say this is the square root of 5 over 2. Okay, let's erase this. So the next one I want, and I'm just going to tighten this down so we kind of make that a little bit neater. So let's move this down a little bit. Okay, so the next one I'm going to do, is going to be my cosine of theta. Okay, my cosine of theta. Again, this is the ca part of this. So cosine is adjacent over hypotenuse. So where is the adjacent? That's 2. What's the hypotenuse? It's 2 times the square root of 5. Before I rationalize the denominator, let's cancel this with this and put a 1 up here. So this is times the square root of 5 over the square root of 5. And this gives me the square root of 5 over 5. Okay. Now I want you to notice that the cosine of theta here, okay, with this angle up there, is the same as the sine of theta here, okay, with the angle here. Again, we'll talk more about this in a moment. So let me flip this guy right here before we rationalize the denominator. The secant of theta is going to be the square root of 5, okay, over 1, but just square root of 5. So let's just kind of tighten this down a little bit so we don't have stuff all over the place. So let's move this down. And then lastly, we're going to have our tangent of theta and then our cotangent of theta, okay? So what's the tangent of theta? That's the TOA part, right? So TOA, opposite over adjacent. So the opposite here, and I erased this, I apologize, this is the opposite here. Opposite is 4, adjacent is 2. So 4 over 2, or 2, okay? And if I flip this guy, remember, if you're flipping a non-fraction number or a whole number or integer, if you want to think about it that way, you just write the number over 1 and then flip it, right? So it would be 1/2. So this is 1/2. And again, if I look at the tangent of theta here, it's going to match the cotangent of theta here. So the tangent of theta here is 1/2, and the cotangent of theta here is 2. Those guys are flipped. So now the tangent of theta is 2, and the cotangent of theta is 1/2. So this is going to lead us to an important result. And we're going to talk now about something called cofunctions. So to talk about these cofunction identities, at least the first time you see them, it can be a little bit challenging to understand. So just stay with me for a moment. I'm going to show you when you get to the examples, they're very, very easy to figure out, okay? So even if you don't fully understand the concept, you can work the problems very, very easily. So the first thing is that we noticed that the sine of theta from the first example was equal to the cosine of theta from the second example. So I have the same triangle here. I've just marked it with different letters. There's no actual numbers here, okay? So we have this lowercase a, this lowercase b, and the lowercase c that's representing the lengths of the sides here, okay? So if we wanted, let's say we had this measure of angle A. So this is angle A. This is what we used in the first scenario. If we wanted sine of A here, okay? If we wanted sine of A, well, what is this going to be? Well, it's opposite over hypotenuse. Your opposite here is the lowercase a. Your hypotenuse here is lowercase c, okay? And then if you wanted the cosine, okay, of b now, okay, of b, so I'm changing the angle up. I'm here now. You're going to notice that's going to be the same thing. It's going to be a over c. And again, lowercase a, lowercase c. Because now this is your adjacent, okay, and this is still your hypotenuse. Remember, cosine is adjacent over hypotenuse. And you'll notice that, again, your sine of theta is the square root of 5 over 5. This is the first example where this is our angle. In the second example, the cosine of theta, here's our angle here, is square root of 5 over 5. So this relationship is always going to be true for the two acute angles of a right triangle. Okay, so since the sum of the three angles in any triangle is 180 degrees, and our angle C here, remember this is our right angle, it's exactly 90 degrees. So that means because the sum of all three angles is 180 degrees, the sum of the measures of angles B and A is going to be 90 degrees, right? These are complementary angles. We've talked about this before. If they sum to 90 degrees, two angles, they're complementary angles. So because these two angles, A and B, are complementary, and our sine of A is equal to our cosine of B, we say the functions sine and cosine are cofunctions. We also say that tangent and cotangent are cofunctions. And then we can say secant and cosecant are cofunctions as well. And if you want to go back, if you look at the tangent of theta here, it's 1/2. And if you look at the cotangent of theta here, it's 1/2. Okay? If you look at the cosecant of theta here, it's square root of 5. And if you look at the secant of theta here, it's square root of 5. So how can we use this for practice problems? These are your cofunction identities. You just need to memorize them. It's something you're just going to plug into. So your sine of your angle A is equal to your cosine of 90 degrees minus your angle A. So for example, if it was sine of 50 degrees, well, you would just say this is equal to cosine of, let me make this a little bit better. So cosine of what? Well, you would say 90 degrees minus 50 degrees, that's 40 degrees, okay? And you can punch this up on a calculator and you see that those are the same. Same deal with cosine of A and sine of 90 degrees minus A, secant of A and cosecant of 90 degrees minus A, so on and so forth. You can copy these down. But basically, if we look at a problem like this, the cosine of 48 degrees, and we want to write it in terms of its cofunction, well, again, you just say, well, this is going to be equal to the sine of, you take 90 degrees minus the measure here, which is 48 degrees, okay? And what's 90 degrees minus 48 degrees? Well, it's going to be 42 degrees, okay? So we can say cosine of 48 degrees is equal to sine of 42 degrees, okay? So this number here and this number here, those guys, because these are, again, complementary angles, they have to add up to 90 degrees. So that's what you want to make sure of, and then make sure your cofunctions there. So cosine and sine, tangent and cosangent, secant and cosecant, so on and so forth. Let's do another one. So we have the tangent of 11 degrees. So again, I would do cotangent, okay, of 90 degrees minus 11 degrees. 90 minus 11 is going to be 79. So this would be cotangent, okay, of 79 degrees there. So the tangent of 11 degrees is equal to the cotangent of 79 degrees. Again, you want to check to make sure that this plus this is going to give you 90 degrees. Okay, so let's look at an example that involves solving equations using cofunction identities. For this guy right here, we're going to find one solution for the equation, okay? And we're going to assume all the angles involved are acute angles. So you'll see a problem like this or a few problems like this in this section. And solving it is very easy. Remember, I told you that this plus this, okay, is going to equal 90 degrees. So all I need to do is take the inside parts, the 2 times theta plus 20 degrees, and add this to the 3 times theta plus 5 degrees, and set this equal to 90 degrees, okay? I'm going to solve for theta, okay, my unknown angle measure. So what I'm going to do here is I'm going to combine like terms. So 20 degrees plus 5 degrees is 25 degrees. And 2 times theta plus 3 times theta would be 5 times theta. So 5 times theta plus 25 degrees is equal to 90 degrees. Okay, so just like I'm solving an equation, just like if I had x there, I want to isolate this guy. So I want this by itself. So how do I do that? I'm going to first subtract 25 degrees away from each side of the equation. So this is going to be gone. I'll have 5 times theta is equal to, what's 90 degrees minus 25 degrees? It's going to be 65 degrees, okay? So to wrap this up, what I'm going to do is divide both sides by 5 so that I can isolate theta. And I'll say that theta is equal to 65 divided by 5 is 13. And of course, you have degrees there for the units. So I would say theta is equal to 13 degrees. Now, if you want to check this, all you would do is plug in. So 2 times 13 degrees is 26 degrees. 26 degrees plus 20 degrees is 46 degrees. So sine of 46 degrees is equal to cosine of what? 3 times 13 degrees is 39 degrees. 39 degrees plus 5 degrees is 44 degrees. So is this true? Yes, it is, right? Sine of 46 degrees is equal to cosine of 44 degrees. Again, this plus this has got to be 90 degrees. And of course, you have your sine and cosine. In this lesson, we want to talk about trigonometric functions of non-acute angles, and also we'll learn about reference angles. All right, so let's start off with a concept of a reference angle. This is something that's very important in trigonometry. So first, from the definition, we're going to say that every non-quadrantal angle in standard position will have a positive acute angle known as its reference angle. So when we talk about the reference angle for an angle theta, it's written as theta prime. So you'll see here we have this theta prime. Okay, so this is your reference angle notation. Now, when we talk about the reference angle for an angle theta, then basically this is the positive acute angle that is made by the terminal side of our angle theta and the x-axis. So I'm going to go through this in each quadrant. In every case, I'm going to be thinking about an angle theta that is between 0 degrees and 360 degrees. If you get something that's outside of that, you're just going to find the coterminal angle that's between 0 degrees and 360 degrees, and you'll apply the little formulas that we're going to look at here. So what I'm going to start with is an angle in quadrant 1. So if I think about the positive acute angle that is made from the terminal side of this angle theta in the x-axis, well, easily I can see that theta here is going to exactly be equal to theta prime. So if you're in quadrant 1, then you can say that theta is equal to theta prime. So your angle theta is going to be its own reference angle. If you're in quadrant 2, you have to do a little bit more thinking. So now I'm thinking about this angle right here. Okay, so this is my theta prime. Let me use a different color that's going to show up here. So this is from the terminal side of this angle theta to the x-axis. So I'm always thinking about going to the x-axis. So that angle has this measure of theta prime. So how do we get this? What I would think about is the fact that if I took this angle measure here, which is a straight angle, the measure is 180 degrees. So I'm going to say in quadrant 2, I'm going to start with that straight angle, which is 180 degrees. And I'm going to say that I need to subtract away the measure of the angle theta, right? So I'm going to take this part away, right? That's what I'm going to subtract away, and that's going to leave me with my theta prime that I'm looking for. Let me get rid of all this so that's more clear. So I'm going to subtract away my angle theta, whatever it is, and let me slide this down here, and I'll say that theta prime, or your reference angle, is going to be equal to 180 degrees minus theta. Again, this is in quadrant 2. All right, if we're in quadrant 3, well, now we have to think about this guy right here. So this is your angle here, and I only want this part right here. So coming from the x-axis going down to that terminal side, that's going to be my theta prime here. So in this particular case, in quadrant 3, we are going to start with our angle theta. So let me say theta prime is equal to our angle theta, whatever it is. And we are going to subtract away this straight angle here. So this part right here, that's what we want to take out. And that's going to leave us with this amount of rotation right there. So I'm going to take away that straight angle, which is 180 degrees. So in quadrant 3, your theta prime, or your reference angle, is your theta minus your 180 degrees. All right, now let's take a look at an angle that's going to be in quadrant 4. So if we think about one full rotation, so this guy right here, that's going to be 360 degrees. So if I'm in quadrant 4, I would start with 360 degrees. And then to get this angle theta prime here, which is going to be this part right there, well, all I need to do is subtract out this angle here, theta, right? I'll be left with my theta prime. So let me actually slide this down just a little bit, and I'll say that theta prime is equal to 360 degrees minus my angle theta. Okay, so we have summarized everything, and basically, when you get to the examples, once you've gone through how it works, you can just use this little table. After you work enough examples of this or get deeper into trigonometry, this is something you're just going to have memorized, and you won't have to consult a table or draw a sketch or anything like that. So I'm going to start out with 330 degrees, and I want to find the reference angle. So I know that this is in quadrant 4. So I look through my little cheat sheet here, and in quadrant 4, again, my theta prime is equal to 360 degrees minus my angle theta. In this case, it's 330 degrees. And so this is just going to be 30 degrees for the reference angle. And again, you can always make a sketch if this is not clear for you. So this would be a 330 degree angle. And a lot of you can just think about that and see that I would need 30 more degrees to get back to the x-axis. So that's your reference angle there. But again, you can also do it where you think about one complete rotation is going to be 360 degrees. So 360 degrees. And then you subtract away the part that you're not going to want to measure. So that's your angle theta there. And in this case, that's your 330 degrees. And that leaves you with your reference angle, which is this part right here, which is 30 degrees, right? So let me put theta prime is equal to this. Okay, for the next one, we have negative 250 degrees. So as I mentioned earlier, if you're not between 0 degrees and 360 degrees, find the coterminal angle. Now, you could do it this way, and a lot of people do, but I think finding the coterminal angle first is just worthwhile because it's just going to make the process easier. You can just use this. So for negative 250 degrees, I would start by just adding 360 degrees to find my coterminal angle, and that's going to give me 110 degrees. So now I'm thinking about a theta of 110 degrees. That's going to be in quadrant 2. So in quadrant 2, your theta prime is equal to 180 degrees minus this 110 degrees, and that's going to give me 70 degrees. So again, if you want to look at a little sketch, we think about an angle with a measure of negative 250 degrees. We're going to show that with a clockwise rotation. So I'm going to start here and go this way. So that guy would be negative 250 degrees. But again, you just work with the coterminal angle, right? So that's a 110 degree angle, same initial side, same terminal side. And so let's get rid of this, and we'll just work with this guy. And again, you can think about this logically. If I start here and I rotate 110 degrees counterclockwise, well, then I need to go another 70 degrees to get to the x-axis, right? 110 degrees plus 70 degrees is going to be 180 degrees or form that straight angle. Again, the other way you could think about it is your theta prime here is going to be your straight angle, which is 180 degrees, minus the part of this rotation that you don't want. So that's this part right here, which is your 110 degree angle. And so that's 70 degrees. Okay, so that's your theta prime or your reference angle. All right, let's look at one more. So now we have 560 degrees. And again, I would find the coterminal angle that's between 0 degrees and 360 degrees. So 560 degrees, let's say minus 360 degrees. And that's going to give me exactly 200 degrees. So this angle right here is going to be in quadrant 3. So in quadrant 3, we would say theta prime is going to be theta, which is 200 degrees, minus 180 degrees. So my reference angle theta prime is 20 degrees. So coming to our little sketch, again, if you wanted to think about it as a 560 degree angle, that's one complete rotation, which is 360 degrees, and then another 200 degrees to get to that point right there. But I just like to work with a coterminal angle. I think it's much easier. In this particular case, you think about the entire rotation here. So let me put theta prime is equal to, that's going to be 200 degrees. And then you want to subtract out the part that you don't want. Again, I'm thinking about from here, the x-axis to here. So that's going to be me taking out this straight angle here, which is going to be 180 degrees. So that gives me my reference angle, or this rotation from here to here, of 20 degrees. All right, so now what we're going to do is talk about trigonometric function values of special angles. So we have these 30 degrees, 45 degrees, and 60 degrees in terms of the angles that we're going to want to memorize the sine, cosine, and tangent values for, and then also your reciprocal functions, so your cosecant, your secant, and your cotangent. So I'm going to start off with a triangle that you should know from geometry. If you haven't taken geometry before, it's not that big of a deal. So this triangle is known as a 30 degree, 60 degree, 90 degree triangle. So this is a special right triangle. And so the side that's opposite of the 30 degree angle has length 1. The side that is adjacent to this 30 degree angle has length square root of 3. And then the hypotenuse here has length 2. So if I wanted to figure out the sine of 30 degrees, and then the cosine of 30 degrees, and then the tangent of 30 degrees, let's go ahead and set those up. So for the sine of 30 degrees, let me make this S a little bit better. Again, it's opposite over hypotenuse. So the opposite side here has length 1, and the hypotenuse has length 2. So this is 1/2. Then for the cosine of 30 degrees, it's going to be adjacent, which is square root of 3, over hypotenuse, which is 2. Now for the tangent of 30 degrees, it's going to be opposite, which is 1, over your adjacent, which is square root of 3. And of course, we would rationalize the denominator there, so multiply by the square root of 3 over the square root of 3. So this is the square root of 3 over 3. So square root of 3 over 3. Now, you could find your reciprocal functions if you wanted to. So you could take the reciprocal of this to get your cosecant of 30 degrees. You could take the reciprocal of this to get your secant of 30 degrees. And you could take the reciprocal of this to get your cotangent of 30 degrees. I'm not going to waste time doing that. I'm going to give you a table where everything's presented. I'm just showing you where this stuff is coming from. I'm going to do the 60 degree angle as well. So let me go sine of 60 degrees. And we know from a previous lesson that that should be equal to the cosine of 30 degrees. So this should be the square root of 3 over 2. And if we check that, well, if I look at this 60 degree angle here, well, the opposite is now going to be the square root of 3, and the hypotenuse is still 2. So square root of 3 over 2. So that checks out. Then the cosine of 60 degrees, again, we know that should be the sine of 30 degrees, so this should be 1/2. So if I look at my cosine of 60 degrees, it's the adjacent, which is 1, over the hypotenuse, which is 2, so I do get 1/2. Then for my tangent of 60 degrees, this is going to be equal to what? Well, again, I would just think about my opposite, which is square root of 3, over my adjacent, which is 1. So square root of 3 over 1 is just going to be the square root of 3. So the other angle that we didn't do was the 45 degree angle. So this is an isosceles triangle. It's the 45 degree, 90 degree. That's a special right triangle from geometry. Again, if you've never seen this before, it's not that big of a deal. I'm just showing you where the things come from. So if I want to write out the sine of 45 degrees, the cosine of 45 degrees, and then the tangent of 45 degrees. So for these two, it's going to be the same. Because let's say I start with this guy right here. Well, it's going to be the same as if I worked with this guy right here. It doesn't matter. They're both 45 degree angles. So if I take this one right here and I say opposite over hypotenuse, it's going to be 1 over the square root of 2. And if I rationalize the denominator, I multiply by the square root of 2 over the square root of 2. So this is the square root of 2 over 2. So this is the square root of 2 over 2. Now, let's say I start here and I say, what's the cosine of 45 degrees? Well, now it's going to be adjacent, which is 1, over your hypotenuse, which is square root of 2. Well, I just did that. So if I rationalize the denominator, it's square root of 2 over 2. And it wouldn't have mattered if I would have used this angle here, I would get the same result, okay? Now the tangent of 45 degrees, you're gonna think about your opposite, so let's use this one. So the opposite is 1, and then over your adjacent, which is 1. And again, if you pick this one, well now the opposite is 1 and your adjacent is 1, so it does not matter. It's 1 over 1, which is 1. All right, so what I've done here is actually summarized all the information into a nice little table. So we already know where this information comes from. We looked at the sine, cosine, and tangent for 30 degrees, 45 degrees, and 60 degrees. For this table over here where we have the cotangent, the secant, and the cosecant for 30 degrees, 45 degrees, and 60 degrees, it's just found using the reciprocal identities. This is something you definitely want to commit to memory. These angles are going to come up over and over and over again, so it's just going to make your life a lot easier. Now, there's something you can search for called the hand trick if you want an easy way of memorizing this. All right, now let's talk about how to find the trigonometric function values when you have a non-acute angle, but your reference angle is still going to be 30 degrees, 45 degrees, or 60 degrees. So we're going to be able to use that table that we just looked at. So I'm going to start with this special right triangle that we looked at earlier. I've just flipped it around such that you can draw this if you want to. It'll make it easier to understand when I put this on the coordinate plane. So this is your 30-degree angle. I just want you to remember that the side opposite of this has length 1. And then your side adjacent to this is going to have length square root of 3. And then your hypotenuse, that length is 2. So what I did here was slap this on the coordinate plane. So you see that this point right here is the origin. And you see that this point right here, we're going to find the x value and the y value. And we'll talk about that in a second. But again, if you wanted to find the sine of this angle, which is 150 degrees, well, basically you would just find that point on the terminal side. And remember, you have sine of 150 degrees is equal to y over r, right? Sine of theta is y over r. Let me write out cosine also. So cosine of 150 degrees is x over r. And then we have tangent of 150 degrees. This is y over x. So we'll look at this in a moment and we'll compare it. Now I want you to notice that you have this reference angle here, which is 30 degrees, right? Again, if you're in quadrant 2, you have this entire guy here, which is a straight angle, that's 180 degrees, and you subtract away the part that you don't want to measure, so that's 150 degrees. So 180 degrees minus 150 degrees is your 30 degrees. So that's the amount of the rotation left to get from the terminal side to your x-axis. Okay, so I want you to think about what would the x value be, what would the y value be, and what would the r value be. So the r value is simple, it's just going to be 2. So r is equal to 2. For your y value, again, opposite of the 30-degree angle, this side has length 1. So if I'm starting here and going here, well, I've traveled 1 unit up, and again, you see the 1 right there, so the y value here is going to be 1. When we think about the x value, notice that we're going left, right? If we go to the left of the origin on the coordinate plane, the x values are negative. So this length right here, we know that side adjacent to 30 degrees is length square root of 3. But again, because we're on the coordinate plane, this is the negative of the square root of 3 for this x coordinate right there. So let's put this right here. So the negative of the square root of 3 like that. Okay, so let me actually write this all out. So the x value here is the negative of the square root of 3. The y value here is 1, and the r value here is 2. We're going to think about these values here, and then we're going to compare them to these trig function values for this reference angle, which again is 30 degrees. So we have y over r. So y is 1 and r is 2. Then here we have x over r. So x is the negative of the square root of 3 over r, which is 2. And then here we have y over x. So y is 1 and x is the negative of the square root of 3. So let me actually rationalize the denominator here. So times the square root of 3 over the square root of 3. So this would be the negative of the square root of 3 over 3. Now I want you to think about these function values that we talked about. With a 30-degree angle, the sine of theta is a half, the cosine of theta is square root of 3 over 2, and the tangent of theta is square root of 3 over 3. So coming back here, you'll see that everything matches in terms of absolute value. Okay, so this leads to an important result. What's going to happen is if you want to find something in quadrants 2, 3, or 4, you just first find the reference angle. Okay, so if it's a reference angle of 30 degrees, 45 degrees, or 60 degrees, you can use your little table. We'll talk about other values later on, but for right now, that's what we're going to work with. So that's your first step. So you would figure out, in this case, what is the sine of 30 degrees? then you would apply the appropriate sign based on your sine rules, right? So we know in quadrants 1 and 2, sine is positive. So here the sine of 150 degrees is a half because, again, the sine of 30 degrees is a half, and it's going to be positive in quadrant 2, so you don't have to make a sign change there. But in quadrant 2, cosine is negative, right? So that's why the cosine of 30 degrees, which was the square root of 3 over 2, is not going to exactly match the cosine of 150 degrees. You have to apply that negative there to account for the fact that cosine is negative in quadrant 2, because in this case, your x values are to the left of the origin, and so they're going to be negative. Then when we think about the tangent of 150 degrees, again, in quadrant 2, you're going to be negative for your tangent value, so you have to take your tangent of 30 degrees, which is square root of 3 over 3, and then slap the negative on there to get your answer here. So let's go ahead and take a look at some examples. All right, so we're going to start out with cosine of negative 600 degrees. So again, I'm going to first find the coterminal angle between 0 degrees and 360 degrees, just to make my life easier. So let me put negative 600 degrees. I'm going to need to add 720 degrees to that. So that's going to give me 120 degrees. So this is what I'm going to work with. So the first thing is, if I have a 120 degree angle, my theta prime, which is my reference angle, is going to be, again, I'm in quadrant 2, so 180 degrees minus 120 degrees, which is 60 degrees. So this is my reference angle. Let me write theta prime is equal to 60 degrees, and we can erase this scratch work. Cosine of negative 600 degrees is equal to the cosine of this 120 degrees. Now, here's where you have to apply a little bit of thinking, and you want to say, well, this is in quadrant 2. Is cosine positive or negative? It's negative in quadrants 2 and 3. So I'm going to put equals here, and then I'm going to put the negative of the cosine of this reference angle, which is 60 degrees. Remember, when you talk about things in quadrant 1, so the 30 degrees, the 45 degrees, or the 60 degrees, everything is positive, right? All students take calculus. In quadrant 1, they're all positive. So that's why you have to apply this negative here to this result. So the cosine of 60 degrees, if you go back to your table, is going to be 1/2. So what we'll do is say this is equal to the negative of, again, the cosine of 60 degrees is a half. So your answer here for the cosine of negative 600 degrees is going to be negative 1/2. Okay, let's look at one more. So here we have the secant of 495 degrees. So again, I would first find my coterminal angle. So 495 degrees. Let's subtract away 360 degrees. And that's going to give me 135 degrees. So when I think about a 135 degree angle, again, I'm going to be in quadrant 2. In my reference angle, my theta prime is 180 degrees minus 135 degrees, which is 45 degrees. Okay, so that's what I'm working with there. So let me get rid of this, and I'll just state that the secant of this 495 degree angle is equal to the secant of this coterminal angle, which is 135 degrees. So this is equal to, if I'm in quadrant 2, secant is going to be negative, right? Remember, secant is the reciprocal of cosine. They're both going to be negative in quadrants 2 and 3. So I'm going to put this negative out in front to account for that. And then I'm just going to think about the secant of 45 degrees. So coming up to my table, if I want the secant of 45 degrees, it's going to be the square root of 2. So I'll say this is equal to, don't forget your negative, so the negative of the square root of 2. In this lesson, we want to talk about finding trigonometric function values using a calculator. We'll also discuss using inverse trigonometric functions to find angles. Okay, so the first topic here is going to be very, very simple. I just want to make sure everybody's on the same page with using their calculator. If you're using an online calculator, you can pretty much just skip this part of the lesson. If you see something like the cosine of 60 degrees, we already know from this special right triangle where we have 30 degrees, 60 degrees, and 90 degrees. If we want the cosine of 60 degrees, well, it's adjacent, which is 1, over the hypotenuse, which is 2, right? As a decimal, this is 0.5. So what I want everybody to do is pull out their calculator that they're going to use for this course, and it should have a sine key, a cosine key, and a tangent key. You want to figure out what mode you're in first. So most calculators have a radian mode. We're going to talk about radians later on. And a degree mode, you want to select degree mode. So you should be able to just hit the cosine key on your calculator. So it would look like that. And then basically you would have some parentheses that would open up, and you just want to type in 60. Don't worry about trying to find the degree symbol. If you're in degree mode, then it knows you're working with 60 degrees. So you hit the enter key after that. So you hit your enter. your enter key after that, and you should get a result of 0.5. If you're not getting 0.5, then either you typed in the 60 wrong or you're in radian mode. So it's very important, if you're not getting the right answer, to investigate and figure out what's going on. A common thing that books will tell you to do is always, before you start working, hit sine of 90 degrees in your calculator. So that's going to look like this. You're going to hit the sine key, and then you're going to put 90 inside of the parentheses. And again, you're just going to hit enter. And then that should produce a value of 1. If you get a value that's something like 0.894, you know you're in radian mode and you need to switch it. All right, so what we're going to do is just run through a few basic problems. Again, just making sure you're on the same page with me. So we have the sine of 170 degrees. So I would just hit my sine key. And then in the parentheses, type in 170. And then you're going to hit your enter key. And this should give you, let's say, approximately 0.1736481777. That's where my calculator cuts off. Usually the book will tell you where they want you to round to. So let's just say we want to round to the nearest 10,000th. So that's 4 decimal places. So 1, 2, 3, 4. Remember, this is the tenths, the hundredths, the thousandths, and this is the 10,000ths. So if I think about it, the digit that follows is a 4. So the 6 would be unchanged, and you could just get rid of all these digits that follow. So the sine of 170 degrees is going to be approximately 0.1736. All right, let's take a look at another example. So here we have the secant of negative 620 degrees. Now there's a few things here. First off, you might not have a secant key on your calculator. The calculator I use does not have a secant key. So you would say the secant of some angle theta, again, using your reciprocal identity, you could say this is 1 over the cosine of theta, since most calculators do have a cosine key. So you can convert this over and say this is 1 over the cosine of this negative 620 degrees. Now, another thing you might be concerned with, you've seen throughout the course, if I got a negative angle or an angle whose measure was greater than 360 degrees, I would always find the coterminal angle between 0 degrees and 360 degrees. Now, you could do that, but if you're using a calculator, you don't have to. This will automatically calculate the value for you. So you're just going to type 1, then the divided by key, hit your cosine key. When the parentheses come up, just type in negative 620. Again, don't worry about the degree symbol. Hit enter, and we're going to get approximately, let me just make a little border here. If I pick up my calculator, I'll say it's negative 5.75, and then I'm going to have 8770483. Now with this guy, again, if you wanted to round to the nearest 10,000th, that's pretty common for most books. Let's see, we have the tenths, the hundredths, the thousandths, and then the 10,000ths. So this is the digit that follows. So the 7 falls in the category of 5 or greater. So I would add 1 to this 7, and then I would cut all these off. So this will turn into an 8. So your answer here for the secant of negative 620 degrees is going to be approximately negative 5.7588. Okay, let's look at cotangent of 670 degrees. So again, you might not have a cotangent key, but more than likely you have a tangent key. So again, from the reciprocal identities, the cotangent of theta is equal to 1 over the tangent of theta. So really, you could just say this is equal to 1 over the tangent of your 670 degrees, like this. And again, you could just follow those steps with your calculator. Hit 1, hit divided by, hit your tangent key. Inside the parentheses, type in 670, and then close the parentheses and hit enter. And so this is going to be approximately, let's say negative, I'm going to go 0.839099, and then we'll have 6312. And again, if you wanted to round to the nearest 10,000th, again, forget about the fact that it's negative. I know that throws off a lot of people. You've got 1, 2, 3, 4 decimal places. So this guy right here, the digit that follows is a 9. So add 1 to this 0, that's going to be 1, and then you can cut all these digits off. So rounding this to the nearest 10,000th, you're going to have negative 0.8391. All right, let's spend a little bit of time now introducing the inverse trigonometric functions. So these are going to be a little bit confusing for right now. When we get further into the course, we're going to spend a lot of time developing the whole thought process behind how and why these guys are going to work. For right now, I just wanted to think about something simple. Let's say you had the sine of 30 degrees. And again, we have our special right triangle here, so we can immediately see that the opposite is 1 and the hypotenuse is 2. So we know this is 1/2. And again, you can type that into your calculator and verify you would get 0.5 or 1/2 as a decimal. Now, what if you typed into your calculator sine inverse? So it's going to look like that, or you might see arc sine. That's another way to denote it. But basically, if you took this part right here, or your answer from this, so let's say I put that in the parentheses, this is going to give you this angle measure back. So in other words, it's undoing what you did here. Here you took sine of your angle, which is 30 degrees, and you want to find the opposite over the hypotenuse. So that gave me 1/2. Here you have the inverse sine, and you're taking your opposite over your hypotenuse, and it's going to kick your angle measure, which is 30 degrees, back out to you. So in other words, you could say that you have sine of theta is the opposite over the hypotenuse. And in this case, you have the sine inverse, which is going to be you plugging in the opposite over the hypotenuse, and you're going to get your angle theta back. But there's a problem here, okay? And it's kind of a big problem, but again, we'll talk about this more later on in the course. If you typed in, let's say, sine of 390 degrees, so this is an angle that's coterminal with 30 degrees, it's going to be in the first quadrant, and it's going to have a reference angle of 30 degrees, well, you would get 0.5 or 1/2. Now, I just saw that if I did sine inverse of 1/2, I get 30 degrees. So I'm not getting my 390 degrees back that I'm looking for. So what's going on? Well, the problem is that sine is not a one-to-one function. We talked about this earlier in our pre-calculus course, where for a one-to-one function to exist, you have to have for each x value a given y value, and for each y value a given x value. So for each x, there's one y, and for each y, there's one x. Well, that's not going to be true with your sine function. So what happens is you have to restrict the domain in order to make it a one-to-one function, and that leads to the fact that if I plugged in 1/2 here, I'm only going to be able to get something in quadrant 1, so that's 30 degrees. If I needed to find something else, well, then I'm going to use the concept of a reference angle, and I'm going to think about where sine is positive. So in other words, I know that sine is going to be positive in quadrants 1 and 2. So really, anywhere in quadrants 1 or 2 where I would have a 30-degree reference angle, well, basically, my sine value is going to be 1/2. If I did sine of, let's say, 150 degrees, that has a 30-degree reference angle, so that's going to be 1/2. If I added 360 degrees to that, I would have 510 degrees. And if I did the sine of 510 degrees, I would also get 1/2, so on and so forth. So if you ever get a question, and we'll see them later on in the course, where it says something like the sine of theta is equal to 1/2, well, there's an infinite number of angle measures there, where if you take the sine value of it, you're going to get 1/2. So generally speaking, when you see these questions, especially in the first part of trigonometry, they're going to tell you that theta is going to be between 0 degrees and 90 degrees. So you're going to be in that first quadrant where 0 degrees and 90 degrees will be included. So let's look at a little example here. So we have sine of theta is equal to 4/5. And here theta is restricted, like I was just talking about, to be greater than or equal to 0 degrees and less than or equal to 90 degrees. Okay, so for this one, again, we would just use our inverse sine function. So sine inverse of this guy right here. So this 4/5. So it's like I'm plugging in the opposite over the hypotenuse, and I'm looking for my theta, and this is going to come from quadrant 1. So I'm going to be good to go in terms of this restriction here. So let's punch this into the calculator. So hit your inverse sine key, hit 4, and then divide it by 5. Close your parentheses, and let me move this over. And I'll say theta is equal to this, and I'll say this is approximately. Let's write out what we have. So 53.1301, and then 0.235. So let's again round this to the nearest 10,000th. So you have tenths, hundredths, thousandths. This is the 10,000ths. So the digit that follows is a 0, so we can just cut all these off. And this is in terms of degrees. So our theta here is going to be about, or you can say approximately, 53.1301 degrees. And again, if you didn't have this restriction here, you could really say that theta could be any angle in either quadrant 1 or quadrant 2, where sine is positive, where the reference angle is equal to this guy right here, right? So there's an infinite number of solutions if you take this guy away, this restriction. All right, so similarly, we have the cosine of theta. This is equal to 2/7. So here, again, we're going to say that theta is greater than or equal to 0 degrees and less than or equal to 90 degrees. So since this is positive, if we use our inverse cosine function, we're going to get something in quadrant 1, so we'll be okay. So I'm going to say that I want my theta to be equal to the inverse cosine, and some people write that as arc cosine like this. And basically, you're just going to plug this in here, so this 2/7, and this is going to spit out my angle, my theta, that will be in quadrant 1. So let's hit our cosine inverse button, and then inside the parentheses, type 2 divided by 7, close your parentheses and hit enter. And this is approximately, let's go ahead and say, I'll just write out everything it gives me. So 73.3984504. That's where my calculator stops. If we want to go to the nearest 10,000th, we have the tenths, the hundredths, the thousandths, the 10,000ths. Well, this guy's a 5 here, so let me add 1 to this, and we'll make this into a 5, and then you can cut these off. And this is in terms of degrees. So we would say that our theta here is approximately 73.3985 degrees. Now again, if you did not have this restriction here, then theta could be any angle that's in either quadrant 1 or quadrant 4, that's where cosine is positive, that has this reference angle. In this lesson, we want to talk about solving right triangles and also look at some word problems that involve angles of elevation and also angles of depression. All right, so let's just jump in and look at our first example. When we talk about solving a right triangle, we're just trying to find all the missing angles and all the missing sides. So in this particular case, we have our triangle here. We're given one side that has a value of 14, and then we're given one angle with a value of 37 degrees. So I know the measure of angle A is 37 degrees. I know the measure of angle C, because it's a right angle, is 90 degrees. You can write that in there. And so if you wanted to figure out what the measure of this angle is, well, you know that the sum of the three angles is 180 degrees. So you could say that 180 degrees minus your 37 degrees plus 90 degrees. This guy right here would be the measure of your angle B. So let's go ahead and crank that out real quick. So 37 degrees plus 90 degrees is 127 degrees. And if I subtract 180 degrees minus 127 degrees, I get 53 degrees. So the measure of this angle here is going to be 53 degrees. Okay, so you can write it like this, or some people will say that the measure of your angle B is equal to 53 degrees like this. So whatever notation your teacher prefers, that's how you want to give it. So I'm just going to erase this so we have some room. All right, so now we want to find these missing sides. So we have this guy right here and this guy right here. Okay, so I always use the information given so that I can get a more accurate answer. In almost every case, you're going to have to round, okay? And just get with your teacher or your assignment to know what you need to round to. So for these guys, I'm going to round to the nearest tenth just to keep it really simple. I'm going to start with the fact that I was given this angle here, which is 37 degrees, okay? So I know that sine of 37 degrees is equal to what? It's opposite over hypotenuse, okay? So the opposite side here is this lowercase a. And the hypotenuse here is given as 14. Remember, the hypotenuse is always across from your right angle, okay? So this guy is going to be 14, okay? So how can we solve for this a here, okay, the lowercase a? We just multiply both sides by 14 to clear the denominator, okay? So we'd multiply by 14 over here and by 14 over here, and this guy cancels with this, okay? Same thing we've been doing forever. So what is 14 times sine of 37 degrees? Well, if you punch that up on your calculator, you're going to get about 8.4. Again, if we go to the nearest tenth. So this guy right here, I'm just going to say that A is approximately 8.4. Okay, so it's approximately 8.4. And I'm just going to write in that it's 8.4 here. Again, we know this is an approximation. Okay, so what about this lowercase b here? What's that going to be? Again, when you work with these problems, try to use the information that you're given, because in some cases, you're going to have to approximate your angle, so you won't have this guy available to you as an exact measure. So I'm going to go with the 37 degrees that they gave me, and I want to think about how can I get this guy right here? So we would use cosine now, because the side here, which is lowercase b, this guy is the adjacent side, and this guy is the hypotenuse. So if I did cosine, okay, cosine of 37 degrees, well, now this is equal to, again, the adjacent. the adjacent over the hypotenuse. And the adjacent is what? It's going to be this lowercase b. And the hypotenuse is 14. Okay, so same deal. Very easy to solve this. Multiply both sides by 14. And what are we going to get? Well, we know that this would cancel with this. And 14 times the cosine of 37 degrees. Again, if you're rounding to the nearest tenth, you're going to get about 11.2. Okay, so let's just say that b here, I'm going to put 11.2. Again, we know this is an approximation. It's not an exact value. So we're going to put that b is approximately 11.2. So we've solved this triangle. Okay, we have a value of 8.4 and a value of 11.2 for those two unknown sides. Again, those are approximations. You've got your 14, which was given. You've got this angle is 37 degrees, which was given. We know this is 90 degrees, that was given. And then this guy we figured out was 53 degrees. All right, so let's look at a different type of problem. Now we're solving a right triangle, but we're given two sides. So if we want to start out by finding, let's say, the measure of this angle A, so the measure of this angle A, what can we do? Well, we're given the adjacent side, okay? We're given the adjacent side. Let me just write that down. This is equal to 4. We're also given the hypotenuse. Remember, this is always across from the right angle. So we're also given the hypotenuse. This is 15.4 here. Okay, so what trigonometric ratio is the adjacent over the hypotenuse? It's cosine, right? The cosine function. So we can go ahead and say that cosine of this angle A is going to be equal to, we would have the adjacent, which is 4, over the hypotenuse, which is 15.4. Remember, we're not done here, okay? We need to solve for A, which is our angle measure. How can we do this? We talked about in the last lesson the fact that you could use the inverse of cosine, okay, to figure out what the measure of this angle was. In other words, I'm going to take my inverse cosine function and I'm going to plug this guy in, okay, the ratio in. So 4 over 15.4. And what I'm going to get out of this is going to be a value that's a measure of my angle A. Okay, and it's going to be approximated. I'm going to do to the nearest tenth. So if you punch this up on a calculator and you round to the nearest tenth, you're going to get about 74.9. So let's just say this is about 74.9. Okay, and this is going to be in terms of degrees. So let me put that there. And let me just erase this. We don't need this anymore. I'm going to say that this is approximately 74.9. Okay, in here, I'm just going to label this and say this is 74.9 degrees. But again, this is an approximation. So let me put my degree symbol there. And then let me label this as 90 degrees. We already know that because of the right angle symbol. Now, what's going to be the measure of this? Again, this is just an approximation, but essentially we know that all three angles here would sum to 180 degrees, or the measure of angle A plus the measure of angle B would sum to 90 degrees. So I could say the measure of my angle B here is approximately 90 degrees minus 74.9 degrees, which is 15.1 degrees. So let me go ahead and just write that in here as 15.1 degrees. Okay, so we have our three angles. Now what I want to do is I want to think about how I can find this guy right here. Okay, so the value of this lowercase a, the unknown side. So what I can do there is just use my Pythagorean theorem. We know that the length of one leg, which is 4 squared, plus the length of another leg, which is going to be a in this case, so that's going to be a, that guy squared, is equal to the length of the hypotenuse, which is 15.4 squared, okay? Now again, you're going to be estimating this. So 4 squared is 16, then plus a squared equals 15.4. If I square that, I'm going to get 237.16. So let me erase this. We're going to be solving for a. So I'm going to subtract 16 away from each side of the equation. Let me scroll down. I'll come back up. So minus 16 over here, minus 16 over here. This is going to cancel. So you're going to have your a squared is equal to, if I subtract away 16 over here, I get 221.16. Let me erase this. And let me just drag this up so we have enough room to work. Let's move this up here. And so what I want to do now is solve for a. Now, normally you would say a equals plus or minus the square root of this guy, right? But you don't need the minus here. You just need the principal square root. So a is going to equal the principal square root of 221.16. So that's approximately going to be 14.9, okay? Approximately going to be 14.9. So let me scroll back up, and we'll write this as our answer. I'm just going to put 14.9 here. So 14.9. And just to make sure everyone knows it's an approximation, I'll say A is approximately going to be 14.9. Okay. In some of these problems, you're going to have units. You might get inches or yards or feet or whatever you're working with. Just make sure you include your units. In this case, we're not given any. All right, let's look at a little word problem now. So when Max is 123 feet away from the base of the school's flagpole, the angle of elevation to the top of the flagpole is 26 degrees 40 minutes. We want to find the height of the flagpole if his eyes are 5.30 feet above the ground. So when you first see problems that involve the angle of elevation or the angle of depression, it's a little bit confusing. What you want to do to clarify things is always draw a little picture. Okay, so that's what I've done here. And so basically you can see that this part right here, remember his eyes are 5.30 feet above the ground. So 5.30 feet above the ground. So that's what this part is right here. If you think about this entire thing, okay, let me change the color here. This is what we're looking for. This height going all the way down. So it includes this 5.30 feet plus the measure of this side A. Okay, so we need both of those, and we need to add them together. Okay, so what we're going to do is we're going to work on this part first. So how can I find this unknown side A? Well, I'm given this angle measure here, which is 26 degrees 40 minutes. Okay, so if I know that I have this guy right here, which is the adjacent side, okay, and I want to find this part right here, which is the opposite side, well, what trigonometric ratio gives me opposite over adjacent? Well, I can use my tangent function, right? So I can say that the tangent of this 26 degrees 40 minutes is equal to the opposite side over my adjacent side, which is 123 feet. Okay, I'm just going to put 123 just to work with the numbers for right now. Okay, so what we want to do is just multiply both sides by 123. And let me scroll down and get some room going. So I'm going to multiply this side by 123 and this side by 123. We know that this cancels with this, and I'm left with just A. Okay, and it kind of looks like a 9, so let me make that more clear. So I would say that, I'm just going to flip this over and say A is equal to, or actually let's put approximately, because we're going to have to estimate this. If I did 123 times the tangent of 26 degrees 40 minutes, I would get about 61.8 feet. So about 61.8 feet, okay? Now, and I could just put FT to abbreviate that. Now, if you're confused about how to enter this into your calculator, you have on a TI-83 or 84, whatever you're using, you can hit secant and then angle, okay? And you can choose degrees and you can choose minutes, okay? That way you don't have to convert it into a decimal and then type it in. It's a little bit easier and it'll be a little bit more accurate. All right, so A is approximately 61.8 feet. Now, we are not done. We haven't solved the problem yet. Let me erase all this and let's go back up. And let's say that this guy is 61.8 feet. But again, I'm trying to find the height of the flagpole, which goes all the way down, okay? Remember, his eyes are 5.3 feet above the ground, okay? So I've got to add these two guys together to get my final answer. So we're going to do 61.8 feet plus 5.3 feet, okay? And this would give me 67.1 feet. In this lesson, we want to talk about converting between radians and degrees. So far in our course, we have strictly measured our angles using degrees. Now, as we progress through this course and math in general, it's going to be more useful to measure angles using radians instead of degrees. This is going to allow us to treat trigonometric functions as functions with domains of real numbers. So what exactly is a radian? Well, a radian is going to be based on the radius of a circle. So I want you guys to recall that the distance from the center of a circle to any point on the circle is known as the radius. So typically we will denote this with a lowercase r. So let's look at this little graph we have here. We have a circle that's already drawn. I have made a point at the center of the circle, and I have made a point just somewhere on the circle. Okay, it's right here, but it could have been right here. It could have been right here. anywhere on the circle, if I draw a line segment from the center to some point on that circle, the distance is always going to be the same, and it's represented with that lowercase r. So if I drew this guy right here, this would have a distance of r, or if I drew this guy right here, this would have a distance of r as well. So let's say that we make a copy of our radius, and we just extend this vertically. So we'd say that this has a distance of r, and now let's bend this onto our circle, again, to where from right here, okay, starting right here, going all the way down to this point, and from right here going to this point here, those both have a distance of r. So we understand what we're looking at here. Now let's suppose that we have an angle where the vertex is at the center of the circle, and it intercepts an arc on the circle that's equal in length to the radius of the circle. So you can see that's the exact situation we have here. We have the center of the circle, that's the vertex of our angle, and it intercepts an arc, okay, it intercepts an arc that is exactly equal in length to the radius of the circle. So when this case occurs, we can say that our angle theta is exactly equal to 1 radian. So 1 radian. Now let's extend this concept to 2 radians. What would an angle of measure of 2 radians look like? Well, we have this here. So now you can see that the angle would intercept an arc that's equal to twice the radius of the circle. This is 2 times r, right? So from right here to right here is r, okay, the radius. This is 2 times r. So from right here to right here, okay, and I can highlight this in. So this is 2 times the radius. So in this particular case, we can say that theta is equal to 2 radians, okay, 2 radians. So on and so forth. You could extend this concept and say if the angle would intercept an arc that's equal to half of the radius of the circle, well then theta would be half of a radian. Again, so on and so forth. So let's talk a little bit about how we can get a formula going to convert between degrees and radians. So in general, if our angle theta is a central angle of a circle of radius r, okay, and theta intercepts an arc of length s, then we can obtain our radian measure of theta by saying that theta is equal to, we would have s, again, this is the length of our arc, divided by r. This is going to be in terms of radians, okay? So if we go back to this example here, well, the length of the arc here is exactly r. So if we said theta is equal to s over r radians, well, now if I substitute in an r there, okay, you would have r over r, which is 1, so you would get exactly 1 radian. If I come to this example here, again, if you say theta is equal to s over r radians, and I plugged in 2r there, so if I plugged in 2r here, so 2r, well, what's going to happen is the r's are going to cancel, and you'd have 2 radians. So 2 radians, so that's where that comes from. So now let's think about this in terms of a 360-degree angle, and we'll use this to build a little conversion formula. So we know that a 360-degree angle corresponds to 1 complete rotation or 1 complete circle. So I can just kind of go over this. This is 1 complete rotation. Okay, so we know that theta here is 360 degrees. Okay, but in terms of radians, what is it? Well, let's think about the fact that the formula for the circumference of a circle, or the distance around the circle, c for circumference is equal to 2 times pi times r. Okay, so this is a formula you should know from basic geometry. If you don't, there it is. So basically, if we think about the fact that a 360-degree angle, which again is 1 complete circle, intercepts an arc equal in length to 2 pi times the radius of the circle, well, if I plug this guy in here, what do I get? Well, in this particular case, theta is equal to, we would have 2 times pi times r over r, this number of radians. So what's going to happen here is that the radius and the radius, those are going to cancel from numerator and denominator. So that's gone, and I'm left with 2 pi radians. Okay, so for a 360-degree angle, it's 2 pi radians. So let's go ahead and erase this and put 360 degrees equals 2 pi radians. Okay, so we're all in agreement on that. Let me just copy this real quick. And let's go to a fresh sheet. So let's paste this guy in here. I'll just drag this down here. Let me just write this in a neater format. So 360 degrees is again equal to 2 pi radians, okay? All right, so what we're going to do now is actually divide this, okay, by 2 on each side. So if I divide this by 2 and this by 2, what I'm going to get, half of a 360 degree angle or half of a full rotation is half a rotation, right? So it's a 180 degree angle or a straight angle. So we would have that 180 degrees is equal to, the 2's would cancel there, right? So I would just have pi radians. And this is the relationship that you're going to see in most textbooks. So let's erase this real quick. And let's drag this up here. And I'm going to show you a few different ways you can think about this. Now, when you work with some type of conversion problem, generally you want to set up a fraction that's equal to 1, where what you want to end up with is in the numerator. So in other words, for these problems, the way I would do it is I would say, okay, you can say 180 degrees over pi radians, okay, like this, if you're trying to convert to degrees, okay? Or if you were trying to convert to radians, you could say that you had pi radians over 180 degrees. Okay, so either of these would work. It's just a matter of what you're trying to cancel. Am I trying to cancel out degrees? Am I trying to cancel out radians? What you want to end up with needs to be in the numerator, so let's keep that in mind. So let's go to the first problem here, and we have 150 degrees. So again, the relationship is that you have 180 degrees is equal to pi radians. So I'm just going to write that down. This is something you should memorize so that you always have that in your head, okay? So if I want to convert to radians, I want degrees in the denominator, okay? So what I'm going to do is I'm going to multiply this by pi radians, okay? Pi radians over 180 degrees, okay? Let's erase this. We don't need this anymore for right now. And let's just think about what's going to cancel. Well, degrees would cancel, so you can get rid of that, okay? And so we know our answer would be in terms of radians. And now I'm just going to go through and say, okay, well, 150 is divisible by 30, right? If I took 150 and I divided by 30, I would be left with exactly 5. If I divided 180 by 30, I would be left with exactly 6. So what I'm going to have is 5 times pi over 6 radians. So 5 pi over 6 radians. Okay, so very easy to convert these guys. And you can erase this, right, just so you can show the relationship. Let me just kind of scooch this over so we can make it nice and neat for our presentation. So 150 degrees is again equal to 5 pi over 6 radians. Let's look at another one. So we have 260 degrees. Again, I'm just going to multiply this by 180 degrees is equal to pi radians. So I want degrees in the denominator, so I want to get rid of that. So I'm going to say that pi radians is going to go in the numerator and 180 degrees is going to go in the denominator. So I'm just going to cancel this with this. Those are gone. And I would say that, okay, 260 and 180, they're each divisible by 20, okay? So I can say that 260 divided by 20 is 13, and 180 divided by 20 is 9. So this would be equal to 13 pi, okay, over 9, this number of radians, okay? All right, so now we have negative 157 pi over 36. This is, of course, in terms of radians. So let me just go ahead and write that in real quick. So this is in terms of radians. And we want to convert this into degrees. So again, I'm going to multiply now. I would want radians to be in the denominator here and degrees to be in the numerator. So 180 degrees would go in the numerator. And then we would put pi radians in the denominator. Again, if you just remember this relationship, 180 degrees equals pi radians. Again, this is because these two guys are equal to each other, this fraction has a value of 1. We're just using it to kind of cancel what we don't want. In this case, we don't want radians, so that's going to cancel. We're going to get rid of pi in each case. And so this is going to be equal to what? Well, you'd have 180 divided by 36, which is going to give you 5. So you have negative 157 times 5 degrees. So this would be negative 785 degrees. Again, if you wanted to make this more presentable, if you're turning this in for a test or something like this, then you could erase all that and just put, let me put radians in here to be clear. So radians, and we'll put is equal to negative 785 degrees, and I'll just erase this here. So negative 157 pi over 36 radians is equal to negative 785 degrees. Okay, let's do one more. Again, a very easy concept. I'm going to say this is in terms of radians. So 43 pi over 12 radians. I'm going to multiply this by what? I want radians in the denominator, so I want 180 degrees in the numerator. Again, I want this in terms of degrees, so I'm going to put pi radians in the denominator, and of course, this cancels, and so what I end up with is, what, 180 divided by 12 is going to be 15, so this will be 15, and that'll be gone, and then 43 times 15 is 645, so this would be 645 degrees. Again, if you want to clean this up a little bit, you just erase all of this. And let me put this back, and we'll just slide this over. We'll say that 43 pi over 12 radians is exactly equal to 645 degrees. In this lesson, we want to talk about how to find the arc length on a circle, and also we'll look at how to find the area of a sector of a circle. All right, in the last lesson, we learned how to measure our angles using radians instead of degrees. So now what we're going to do is we're going to take our little formula, and we're going to get a formula for finding the arc length on a circle. So let's recap what we learned in the last lesson. So if our angle theta is a central angle of a circle of radius r, and theta intercepts an arc of length s, then we can obtain our radian measure of theta as, we say that theta is equal to s over r, okay? Now in this first example, what I've done is I've made this arc length equal to r exactly. So this guy right here is the same as the measure of our radius, okay? So when this happens, you can plug in an r in the place of s. R over r is of course 1, right? If we said this is r over r, this is equal to exactly 1. So the measure of your angle theta in this particular case is 1 radian. Now, in many cases, you're not going to have a measure of 1 radian, okay? So now our arc length here is going to just be represented with s, okay? So it's no longer equal to r. So in this case, we just go back to that little ratio, and we say that theta is equal to s over r, okay? So s over r. But what this is telling me is that I could rearrange this equation, okay? And I could solve for s. Given the fact that I know the measure of my angle theta in radians, and I know r, which is the length of my radius. So what I do is just multiply both sides by r, okay, by r, and I'm going to get my formula, which is that s, again, that's the length of the arc here, is going to be equal to, this cancels, so I would have r times theta, okay? And theta has to be given in radians for this to work. If you get something in degrees, you just need to convert it, or you could use another formula from geometry, which I'll cover in a little while. All right, let's go ahead and take a look at an example. So we have an angle here which is marked as theta, and theta is going to be equal to, in terms of radians, pi over 4, okay? And then we have our radius r, okay? So r is going to be equal to, we're going to have 12 miles here. So I'm just going to put mi to abbreviate miles. So what we want to do for this problem is find the length of this arc here, okay? Find that length. So again, how do we do this? We're just going to use our little formula. We're going to say that s, okay, I'll mark this with s, is equal to what? It's equal to r, this radius measure, okay, which is 12 miles in this case, times theta, okay? And theta in this case is pi over 4, okay? So very, very simple math here. I'm going to cancel this 12 with this 4 and get a 3. And basically what I'd have here is 3 pi miles, okay? So s here is equal to 3 pi miles. And you could write out miles or you could put mi. It doesn't really matter. I think I'll just stay consistent and put mi there and leave it as an abbreviated version. Now, depending on the context of the situation, you might want to give it an exact answer like this, or you might want to punch up 3 times pi into a calculator and get an approximation and write it that way. It just depends on what your teacher's asking for. Okay, let's take a look at another example. So let's suppose that now our angle theta here, okay, is given as 135 degrees. Okay, so now we're working with degrees. And then r, the radius, let's say that this is 12 inches. So 12 inches. Again, I'm just going to abbreviate that. So what do we do here? Well, one strategy, if you want to use the formula that we just talked about, is to first convert this into radians. So remember how to do that. Pi radians is exactly equal to 180 degrees. So I would say 135 degrees times. Remember how to do this. You want the units that you want to cancel in the denominator. So I'm going to put 180 degrees down here, and I'm going to put pi radians up here. You don't need to write radians. So I'm going to cancel this with this, so degrees are gone. So the answer I get here is going to be in terms of radians now, okay? So let's think about 135 and 180. What's going to be common between the two? Well, each would be divisible by 45. If I divided this guy by 45, I would get exactly 3. If I divided this guy by 45, I would get exactly 4. So this turns out to be 3 pi over 4 in terms of radians, okay? So I'll just erase this real quick. And I'm just going to erase 135 degrees and put 3 pi over 4 for radians. And now we're basically good to go. Again, we're trying to figure out what is the length of this guy, okay? And I'm just going to mark that and say that this is S, okay? So S is going to be equal to, again, just multiply these guys together. So 3 pi over 4 times 12 inches, okay? And again, what's going to cancel here? 12 cancels with 4 and gives me 3. So you're going to have 3 times 3, which is 9, times pi times inches. So you can say this is 9, okay? This is 9 pi inches. Again, you can write that out or leave it abbreviated, whatever you want to do. All right, so before we move on, I just want to talk a little bit about how you can do this with it being in degree mode. Okay, it's a very simple formula. All you want to do, you probably remember this from geometry, but you just want to take 135 degrees and divide it by 360 degrees. So in other words, you're taking 135 degrees, which is the measure of this angle, okay, and dividing it by 360 degrees, which is the measure of one complete rotation, right? The angle that's formed by a complete circle. And then I would just multiply it by, remember the circumference of the circle is the distance all the way around, okay? So the formula for that is going to be 2 times pi times r, okay? So if we do 135 degrees divided by 360 degrees, your units would cancel. 135 and 360 are each divisible by 45. If I divide this by 45, I get 3. If I divide this by 45, I get 8, okay? So let's just write this as 3/8. Let's just write this as 3/8 times this guy. So now I know that I can cancel this 8 with this 2. That would give me a 4 down here. The r here, if I plug in for r, it's 12 inches, right? So this is times 12 inches. So what else can I do? I can cancel this 12 with this 4, and I'm going to get a 3. And if I multiply across, I'm going to get 3 times 3, which is 9, okay, times pi times inches. So I would still get an S that's equal to 9 pi inches. So it's the same thing, and we can write it out and say that it's the same thing as this. So S is equal to 9 pi inches, right? So those guys are the same result. So either way you want to do this, it's going to give you, again, the same result. It's just a matter of which way you prefer. All right, what we want to do now is talk about how to find the area of a sector of a circle. So we've already seen that a complete circle, or one full rotation, forms an angle with a measure that's 360 degrees, or in terms of radians, it's going to be 2 pi radians. So you can see this guy, one complete rotation or one complete circle, it's 2 pi radians, okay? Now, if we think about the formula for the area of a circle, most of us know this from geometry, the area of a complete circle here is pi times the radius squared. So now, what if we wanted the area for a piece of the circle? Okay, so not the whole thing. So a sector of a circle is the portion of the interior of a circle intercepted by a central angle. So visually, you can see on the screen, this looks like a piece of pie, okay? So how do we find the area for this guy right here? Well, let's think about the formula, and I'm just going to put A for area. Let's think about the formula for a whole circle. Again, it's pi times r squared. Okay, so now that's for a 360 degree angle, or again in radians, 2 pi. Okay, so what I do here is I think about the fractional amount of this guy. So I can take theta, okay, which is the measure of this angle in radians, and divide it by 2 pi, which is the measure of, again, a complete circle or one full rotation in terms of radians. So if I multiply this fractional amount here by this area of a circle formula, I'm going to be good to go, okay? Now notice that you can cancel this with this, and I can say that the area is going to be equal to what? Let's go ahead and say this is 1/2 times, we'll do theta times r squared. And there's different ways to write this, but most textbooks will write it in this way, so that's how I'm going to present it. Now, what's important here is that theta be a central angle, okay? And that the theta also be given in terms of radians. If it's not, again, you've got to convert from degrees to radians to use this formula. All right, let's take a look at an example. So we have our angle theta, we have our radius r. Theta is going to be given to us as 3 pi over 2. The radius r is going to be given to us as 9 meters. You can write out meters or you can just put m for meters. That's the abbreviation. And again, what are we trying to find? We want to find the area of inside of here. Okay, and I'm not going to highlight this perfectly, but you get the idea. Okay, so we're trying to find that area. Now let me just erase that. So how do we do this? Again, we're just going to use the formula. So again, the formula here, you can write A for area. We'll say this is 1/2 times r squared times your theta. Okay, so I'm just going to plug in. What is r in this case? It's 9 meters. Okay, so your area would be equal to 1/2 times, I'm going to plug in 9m, m is for meters, and both of those are going to get squared. Remember, you got to square your units as well. And then times your theta, which is 3 pi over 2. Let me scroll down a little bit and get some room going. So my area here is 1/2 times, the 9 gets squared, it's 81. The meters get squared, so you could write this as square meters or meters squared, or you could just put m squared for short, so m squared. And then times your 3 pi over 2. Okay, so can we cancel anything? No, it doesn't look like we can. So we're going to say that the area is going to be equal to, we're going to say that 81 times 3 is 243. Okay, then times your pi, and then this will be over, 2 times 2 is 4. And this will be in terms of square meters, where you can just write m squared. Again, m is the abbreviation for meters, and we know it's being squared. Okay, so you could write meters out and square it like that. You can put square meters or meters squared if you want to write it out. Any of those would work, but make sure that you square the units and you show that in some way. All right, let's take a look at one more. So suppose now that theta is given to us as 60 degrees, and the radius r is going to be given to us as 13 yards. So I'm going to put YD to abbreviate yards. So let's go ahead and say that the area, again, is equal to 1/2 times your theta times your radius squared. Now, again, theta has to be given in terms of radians, okay? So we need to convert this guy into a radian measure. So I'm going to take 60 degrees and multiply it by, remember, pi radians equals 180 degrees. So I'm going to put pi up top. I'm going to put 180 degrees at the bottom, and I'm just going to cancel. Okay, so this would cancel with this and leave me exactly 3. Okay, so this would be pi over 3. This would be pi over 3. Okay, so let's erase this, and let's think about this now. So we're going to have the area is equal to 1/2 times, you've got your pi over 3, times the radius, which is 13 yards being squared. So don't forget about those units. It's very important. So we're going to say that the area is equal to, can anything cancel? No. So I'm just going to go ahead and say that 13 squared is 169. So this would be 169 times pi, okay, I'll deal with the yards in a moment, over your 6. And then yards squared, again, you could write square yards, you could write yards squared, however you want to do this. I'm just going to put YD for the abbreviation of yards. And then I'm going to put a squared like this. So the area here would be 169 pi over 6 square yards, or again, yards squared. In this lesson, we want to talk about the unit circle and circular functions. All right, back in our algebra course, we learned how to graph a circle, and we also learned how to work with the equation of a circle. So we have here a unit circle, and the center here is at the origin, and the radius is going to be 1. So the equation for this circle is going to be x squared plus y squared is equal to 1. So again, this has a center at the origin. So there's my center. It's at the origin. It's going to be the point 0, 0. And my radius is going to be 1. So that tells me that the distance from the center to any point on that circle is going to be 1 unit. Okay, so from the center here to this point here, if I move 1 unit to the right, this is the point 1, 0. Okay, so I've moved just 1 unit to the right. If I move from the center 1 unit up, this is the point 0, 1. If I move from the center 1 unit down, this is the point 0, -1. And lastly, if I move from the center 1 unit to the left, this is going to be the point -1, 0. Okay, but the main thing to understand is that the distance from the center to any point on that circle is 1 unit. Now, using the unit circle to work with our trigonometric functions will lead to some interesting results that allow us to quickly solve problems as we move forward in trigonometry and also into calculus. So let's just get started here on our unit circle. We have an angle that's in standard position. So basically this is the initial side and this is your terminal side. So your terminal side of this angle theta, okay, is going to lie in quadrant 1. And notice we have a little point here, and this point is going to be labeled as x, y, just generically. You could use a, b, or whatever you want. And that point there is going to lie both on the unit circle and on the terminal side of our angle. So if we wanted to find something like sine of theta, so sine of theta, what would this be? Well, we know when we started this course, we had a definition that was y over r, but you could also use opposite over hypotenuse. It doesn't matter, you're going to get the same thing here. But basically, we know that this guy, right, if we look at this guy from here to here, this has a length of y, right? Because this coordinate is y, this coordinate is 0, right? So this vertical distance here is y, right? Y minus 0, that's all you're doing. So if I think about this, r, the radius, which is my hypotenuse here, okay, is going to be 1, right? Because we're on the unit circle, the radius is 1. So again, the distance from the center to any point on that circle is 1. So sine of theta is going to be y over r, which is y over 1, which is just y, okay? So sine of this angle theta is just going to be the y coordinate of this point right here, okay? And then the same thing is going to happen when I work with cosine of theta. Remember, this is x over r, or again, you could say adjacent over hypotenuse, okay? And in this case, the length here from right here to right here is going to be x, okay? So it's just x over r, which is x over 1, which is x. So the cosine of theta is just going to be the x coordinate for this point right here. So what we can do is really label this point right here as the cosine of theta and then the sine of theta. So again, this is your x coordinate and this is your y coordinate. All right, so let's quickly talk about the concept of circular functions. Basically, all we're going to be doing here is swapping out theta for s. Okay, so how does this work? Well, when we're working with a unit circle, remember that the radius is 1. The formula for our angle theta in radians, remember it comes as theta is equal to s, which is the length of the arc, okay, divided by r, which is your radius. Well, in this case, the r is 1. Okay, the r is 1. So theta will be equal to s. So when we're on the unit circle, our trigonometric functions of our angle theta, measured in radians, found again by choosing some point x, y on the unit circle, can now be rewritten as functions of the arc length s, some real number. Okay, so when we show it in this way, the functions are known as circular functions. So you'll probably see this in your book. They're going to use this letter s instead of theta. Right, so they'll start saying sine of s is equal to y. And then cosine of s is equal to x. And then you can get the rest of them using these. So you could say tangent of s is going to be y over x. And then you can get the rest using the reciprocal identities, right? So the cosecant of s is 1 over y. The secant of s is 1 over x. And the cotangent of s is x over y. All right, so let's talk about how we can set up our unit circle now. So basically in quadrant 1, we're going to rely on these trigonometric function values of special angles, right? We've talked about this before. So we know, and I'm just going to go through a few of these. So the sine of 30 degrees is a half. And we know the cosine of 30 degrees is square root of 3 over 2. So let's just take that real quick. Let's go down to a sample unit circle. It's not all filled out, just part of it, so I can show you where things are coming from. And if we look at a 30-degree angle, which is in terms of radians is pi over 6, we see that the x-coordinate is the square root of 3 over 2, and the y-coordinate is 1/2. Remember, because we're on the unit circle, we have this property. This x-coordinate here is the cosine of this angle. You could say it's 30 degrees, or you could say it's pi over 6 radians, whatever you want to use, it doesn't matter. And in this case, the sine here is going to be your y-coordinate. So the sine of 30 degrees is 1/2. That's your y-coordinate. Again, the cosine of 30 degrees is your x-coordinate. It's square root of 3 over 2. Okay, so using the same logic, you can see that if I'm working with a 45-degree angle or pi over 4 radians, this would be my cosine, and this would be my sine. Okay, if I'm working with a 60-degree angle or pi over 3 radians, this guy right here, this would be my cosine, the 1/2, and this would be my sine, the square root of 3 over 2. Okay, so the point that's associated with that angle, okay, the x-coordinate is the cosine, the y-coordinate is the sine. Okay, so very important to remember that. So once we have this guy set up, there's a lot of different tricks or techniques to remember these 3 different values here. Some people use the hand trick. There's all kinds of stuff out there. I'm going to show you what I learned a long time ago. There's a lot of videos that do it this way as well. What you'd want to do is set up, in each case, a denominator of 2. So a denominator of 2. A denominator of 2. Okay, so that's going to be everywhere. You'll notice you have 2, 2, 2, 2, 2, 2. That's very easy to remember, okay? Then the next thing you want to do, you'll notice that if you ignore the square root symbol, you start here with 1 and you're counting down, and you start here with 1 and you're counting up. So I'm going to make all the numerators like this. So 1, 2, 3, and then I'm going to go 1, 2, 3. Okay, if you get lost about where you want to put the 1 and start and go down, all you need to do is think about, okay, well, if I'm going from right here to right here, okay, if I'm making a right triangle, this x distance is greater than this y distance, okay? So that tells me that I would want the 3 here. And I know it's square root of 3, but just forget about the square root symbol for now. I know this would be greater than this, so I would start with a 3 here, or you could say I'd start with a 1 here. However you want to remember that, you're going to have a 1, a 2, and a 3, and then a 1, a 2, and a 3, okay? So that's a little technique you can use. There are many others that you can go with. Now, once you're finished with that, you want to square root all of the numerators, okay? And if you have the square root of 1, remember that's 1, so you can skip those. So I'm going to have square root of this, square root of this, square root of this, and square root of this, okay? Remember the 1 here and the 1 here, square root of 1 is just 1, so you can just ignore it. Okay, so now we have all of these guys, and you can wrap it in parentheses to make it official if you want, but that's how I get these points there. So now that I have all of these points, what I want to do is reflect across the y-axis to get these points over here. So let me show you this. And basically, if I'm reflecting across the y-axis, think about this for a moment. If I go across the y-axis like this, the y-coordinate is the same. Okay, so you'll notice here you have square root of 3 over 2, and here you have square root of 3 over 2. So that's the same. The x-coordinate is now its opposite, right? Because I'm on the opposite side of the y-axis. Over here, x values are negative. Over here, x values are positive. Okay, so this is negative 1/2 now instead of 1/2. This is negative square root of 2 over 2 instead of square root of 2 over 2. This is negative square root of 3 over 2 instead of square root of 3 over 2. Okay, so it's very easy to just reflect these guys across. Okay, and I know these lines I'm drawing are not perfectly straight, but just pretend they are. So once you've done that, now you can reflect these guys across the x-axis, and you'll have all your points. Okay, so now if you think about a point that's up here, if I reflect it across the x-axis, the x value will be the same, but the y value will be its opposite. So if I reflect this guy right here down there, and I know that line's not perfectly straight, but you have 1/2 and you have 1/2. So the x value is the same. Then you have square root of 3 over 2, and then the negative square root of 3 over 2. So that's all we're doing here to get these values. Again, if you can just remember these values in the first quadrant, okay, you're going to be good to go. You can use the reflection, okay, across the y-axis and then across the x-axis to get all the remaining points. Okay, so let's go ahead and take a look at just a few examples. So I want to look at the sine of 3 pi over 4. And then I want to look at the cosine of 3 pi over 4. And then lastly, I want to look at the tangent of 3 pi over 4. Okay, so we know that we could solve this using methods without the unit circle, right? We already know how to do this. But using the unit circle, it's going to be a little bit quicker. So I'm going to find 3 pi over 4 on my unit circle. So where's that going to be? 3 pi over 4 is going to correspond to a 135-degree angle. So it's this guy right here. And you can see that you have the negative of the square root of 2 over 2. So that's your cosine. Let me write that out. Your cosine of 3 pi over 4 will be equal to the negative of the square root of 2 over 2. And then you have your sine of 3 pi over 4 is equal to the square root of 2 over 2. Okay, so let's copy this real quick. Come back down here. I'm just going to paste this in. So let me just rewrite this. So this would be the square root of 2 over 2. And this guy would be, let me just erase this. I can just drag this over. It's the negative square root of 2 over 2. Okay, so how do I get my tangent here? Well, remember, the tangent is found by taking the sine and dividing it by the cosine. So I would take the square root of 2 over 2 and divide it by this guy. But if I'm dividing fractions, I want to multiply by the reciprocal. So I'm going to flip this guy. I'm going to put the negative out in front. I'm going to flip this guy and put 2 over the square root of 2. And you're going to notice that this will cancel with this will cancel with this, and you're left with negative 1. Okay, so my tangent of 3 pi over 4 is negative 1. All right, let's take a look at another example. So suppose we had something like the sine of, let's say, 13 pi over 6. And let's also do the secant of 13 pi over 6. And let's also do the cosecant of 13 pi over 6. Okay, so if you get an angle that measures, that's larger than 360 degrees or 2 pi in terms of radians, again, what you want to do is find a coterminal angle that's between 0 degrees and 360 degrees, or 0 and 2 pi radians. So if I'm working with radians, what I'd want to do, let me just kind of divide this workspace up here, and I'll just move this over for right now. What I want to do is say I have 13 pi over 6 radians. If I subtract 2 pi away, I would get a common denominator, so I'd multiply this by 6 over 6. So this would end up being what? It would end up being 12 over 6, right? 12 over 6 is the same thing as 2. So what I'd have here is pi over 6 radians, okay? So I would look at pi over 6 on my unit circle, and that's going to be right here, okay? So this is pi over 6. Again, if I went one more revolution around, I would end up with an angle that has a measure of 13 pi over 6 radians, or 390 degrees, okay? So my cosine of pi over 6 is going to be the square root of 3 over 2. And then my sine of pi over 6 is going to be 1/2. Okay, so let's go ahead and copy this. And so I'm going to write that the sine of 13 pi over 6 is going to be 1/2. Okay, because it's exactly equal to this here. Then for the secant, it's the reciprocal of my cosine. Okay, so this would be equal to, I would flip this guy, I would have 2 over the square root of 3. Okay, you just erase this, you don't need this anymore. And so what I do here is just rationalize the denominator. So times the square root of 3 over the square root of 3. So this would give me 2 times the square root of 3 over 3. Okay, then for my cosecant, I'm going to flip my sine, right? So if I flip that, the reciprocal of 1/2 is just going to be 2. All right, let's just do one more example. So I'm going to look at the sine of, let's do negative 23 pi over 4. Let's also do the cosine of the same guy, negative 23 pi over 4. And let me just kind of move these up and out of the way. And then let's also do the cotangent, okay, the cotangent of, let's do negative 23 pi over 4. Okay, so now that we have a negative angle, remember, if you have a negative angle, you want to do the same thing. You want to find a coterminal angle. In terms of radians, it would be between 0 and 2 pi radians. So what I'm going to do is I'm going to add 2 pi radians until I get into that range. So let's go to a fresh sheet and say I have negative 23 pi over 4. If I add 2 pi radians, well, 2 pi to this, again, I want a common denominator. So I would multiply this by 4 over 4. So you could say this is 8, okay, 8, and then 4 down here. Okay, so 8 pi over 4 now. So would this get me where I need to be? No, so I could add another 2 pi radians. So I could add another 8 pi over 4. Again, all I'm looking for is for this guy to not be negative, right? It's got to be between 0 and 2 pi, okay? So if I add 8 plus 8, that's 16, that's not going to get me there. So I need to add another one. So let me kind of scooch this down. So let me add another 8 pi over 4, and that would get me there, right? So 8 plus 8 plus 8 would be 24. 24 minus 23 would be 1, okay? And you can do this with one common denominator and say that you have negative 23 pi plus, again, 8 plus 8 plus 8 is 24. So this would be 24 pi all over the common denominator of 4. So this would end up giving me 1 pi, or just pi, over 4 in terms of radians. So this is my coterminal angle. So let's go find that guy. So on the unit circle, if I look at pi over 4 in terms of radians, or 45 degrees in terms of degrees, it's square root of 2 over 2, and then square root of 2 over 2. So that's really easy to remember. So I know the sine of this guy would be the square root of 2 over 2, okay? And the cosine of this guy would be the square root of 2 over 2. Now what about the cotangent? Remember, the tangent is sine divided by cosine. Well, the cotangent, you flip that, it's the cosine divided by the sine. But in this case, I have the same thing divided by itself either way you go, either for the tangent or for the cotangent. So in each case, this is just going to be equal to 1. In this lesson, we want to talk about linear and angular speed. So previously, we talked about how to solve motion word problems using our distance formula. So that's the d for distance is equal to r, which is the rate of speed, times t, which is the amount of time traveled. So we're going to relate this formula to linear speed, which we'll talk about in a moment. Basically, if we know our rate of speed and we know our time traveled, we know our distance. So for example, if I plugged in 80 miles per hour here, and I plugged in, let's say, 3 hours here, what would be my distance traveled? So we sit in a car, we're moving at 80 miles per hour. We do this for 3 hours. We know that we would do 80 times 3 or 240. This would be 240 miles. Okay, so this is the distance traveled. Now let's suppose we didn't know the rate of speed, but we did know the distance traveled, and we knew the amount of time it took to travel that distance. So now what I could do is I could solve this formula. If I had d is equal to r times t, I could solve it for r, right? And I could plug in and find out what r is. So this would give me, this cancels, the rate of speed is equal to the distance traveled divided by the amount of time it takes to travel that distance. So let's erase this, and let's think about these numbers again, just as a simple example. So suppose my distance again is 240, and this is going to be in terms of miles. Let's suppose my time again is 3 hours. So now if I have this information given, what's my rate of speed? Again, 240 divided by 3 would give me 80, okay? And in terms of units, miles and then hours, you'd have miles per hour. So miles per hour, okay? So very easy to understand this concept. Just think about all the times that you've traveled on a road trip and you've calculated how far you're going to be at what time, okay? So let's erase this, and I'm just going to drag this up here, and I'll talk about how this is related to linear speed now. So for linear speed, let's look at our little diagram here. I want you to suppose that some point P, okay, so this is my point P. It's going to move at a constant speed along a circle with this radius of r, okay, and with a center of O, okay? So the measure of how fast the position of P is changing is known as the linear speed, okay? So instead of r, we're going to use v, okay, for velocity, and instead of d, now because we're traveling along a circle, remember, when you think about the distance or the length that you're traveling on a circle, this is the arc length, right? So we use s for this. So now I'm going to have s over t, okay? So that's how these two guys are related. Instead of r, we use v for velocity. Instead of d for distance, we're going to use s for the arc length that's traced by this point P at the time t. To put this in more simple terms, the linear speed is just the speed at which a point on the outside of some object travels in a circular path around the center of that object. Now, when we talk about angular speed, we're talking about how fast the measure of the angle is changing. So again, if I think about this point here, P, right? So this is the terminal side of the angle, POB. If I'm rotating P around this circle, the measure of the angle is changing, okay? So how fast the measure of that angle changes, that's our angular speed, okay? So this is given by the formula you're going to use this letter omega, okay, and I'm terrible at writing it, but this is the Greek letter omega, and it's equal to theta, okay, which is the angle measure in radians, divided by t, which is your time. Now, there's one more thing I want to talk about before we get to the problems. You might want to make a little substitution, okay? Based on what you're given in the problem, you might want to make a little substitution here. And instead of saying s the arc length, remember the arc length s is equal to your theta, okay, your angle theta that's in radians, times your radius, that length r, okay? So if we plug in there, we could say v is equal to, you would have your theta times r, okay, over t. Now, we know from fractions that I could really rewrite this as r times your theta over t. So now we can make a little substitution because theta over t, okay, is this guy right here, okay? It's the Greek letter omega, which again is our angular speed. So I can put this as my angular speed here. So the linear velocity, or the linear speed, however your book says it, is going to be equal to the length of your radius times your angular speed. So let's go ahead and look at an example. So the tires of a bicycle have radius 15 inches and are turning at the rate of 230 revolutions per minute. How fast is the bicycle traveling in miles per hour? Okay, so the first thing you want to do for a problem like this is calculate the angular speed. So again, I'm going to try to make the omega, okay? And this is equal to, again, theta over t, okay? So the first thing you might notice is that you're given this rate here of 230 revolutions per minute, okay? When you think about one revolution, it's one complete circle, or 360 degrees, or 2 pi radians. Since we're working with radians here, we want to put 2 pi up here. Okay, this is one complete revolution, or one complete circle. We have 230 of these, so I'm just going to multiply this by 230. Okay, so again, this is one complete circle, or one complete revolution, or one complete rotation, however you want to think about that, okay? So it's 2 pi, okay, or 360 degrees if you want to relate it back to degrees. Then we have 230 of these guys, so that's why I'm multiplying by 230. Now, I'm going to divide this by, the time is given as per minute. So per minute means 1 minute there, okay? So this is in terms of radians, so you can write this as radians, okay, right here. So this is 2 pi times 230, or you could say 460 pi radians per minute. Now, the next thing we want to do is think about the time units that we want. It's going to ask for this in terms of miles per hour. We have radians per minute, okay? So we want to convert this to radians per hour. So let me erase this so we have a little bit more room to work, because this can get quite messy. So let's move this down a little bit. And I want to multiply this now by what? I want hours in the denominator. I want one single hour because I want per hour, okay? So if you always think about what you want, go ahead and put that there first. And then how do I get there? I want minutes to cancel. What's the relationship between hours and minutes? Well, 60 minutes is equal to 1 hour. Okay, so now this is basically equal to 1, okay? So what I can do is I can cancel this with this, and I'm left with the units that I want in my denominator. So let's go ahead and multiply 460 by 60, which is 27,600. Don't forget the pi there. It's easy to forget it. Pi, and then you have radians, okay? And then per 1 hour. Okay, so that's your angular speed. 27,600 pi radians per hour. Okay, so let's erase this. I don't need these intermediary steps anymore. And let's just bring this up here. And I'm just going to say it's 27,600 pi, and then I'll put radians per hour. Okay, I'm just going to abbreviate there. Now, let's think about now the linear speed, okay, in terms of miles per hour. So how are we going to get this? So v is your linear speed. Remember the formula we looked at when we plugged in here, we said that we could do the radius times the angular speed. So if we come back down here, the angular speed, I'm going to put 27,600 pi, okay? And then you can go per hour. Let's put this down here. And then times, what's the radius? Well, the radius is going to be given to us here as 15 inches. So 15 inches right here. If I multiply this out, and let me scroll down and get some room going. If I multiply this out, I'm going to get that 414,000 pi, okay? And then we'll say inches per 1 hour, okay? This is not what I want, though, because I want it in terms of miles per hour, and I have it in terms of inches per hour, okay? So I've got to do another unit conversion, and this is where these things get kind of tough. So if you know the relationship between inches and feet, 12 inches equals 1 foot, and then you can convert from feet to yards, and then from yards to miles. I'm going to shorten this up. So the relationship between inches and miles, 63,360 inches is equal to 1 mile. So what I can do, I want inches to go away. So I'm going to put 63,000, and then it's going to be 360 inches, okay? I want that to go away, so I want that in the denominator. And I'm going to put 1 mile in the numerator. Again, 1 mile is equal to 63,360 inches. So this is really a fraction that has a value of 1. Okay, so this would cancel with this. So those units are gone. So now this is going to be in terms of miles per hour. Okay, so what you'd want to do is really just take 414,000 pi, okay, and then divide it by this number here, 63,360. It's going to be an approximation because you're going to get a decimal number. But if you wanted to simplify this first, you could divide this by 720, okay, and you could divide this by 720, and that would give you 575, and this would be 88, okay? So you could really write this as 575 pi miles, okay, per your 88 hours. But again, this is kind of useless because we want miles per hour. So if you punch this up on a calculator, you could say that this is about 20.5. This will be in terms of miles per hour. Okay, so that's our linear speed. So let me just erase all of this. So to answer this with a nice little sentence, I'll say the bike is traveling at about, because again, this is an approximation, 20.5, and this is in terms of miles per hour. So the bike is traveling at about 20.5 miles per hour. All right, let's take a look at one more problem. So at a local high school, Max rides his cart around a circular track at 2 revolutions per minute. If the radius of the circular track is 150 meters, how fast is Max's cart traveling in meters per second? Okay, so a similar setup, I'm going to use omega, once again, to say it's theta over t, right? So this is my angular speed. So what is theta in this case? Well, we have 2 revolutions, and this is per minute. So down here, this would be, let me put t as 1 minute and get that out of the way. And I'm just going to abbreviate it. For theta, it's 2 times 2 pi. Again, 1 revolution or 1 time completely around a circle is 2 pi radians or 360 degrees. So you have 2 pi, okay, times you've got 2 of these revolutions. So 2. So this would be 4 pi radians per minute. Okay, so that's your angular speed. Now we want this in terms of seconds, but let's convert this in a moment because it's going to be a little bit easier for us. We know that with the linear speed, okay, if we're trying to find out how fast Max's cart is traveling in meters per second, well, what I do is I take this guy right here, okay, and I plug it in, and I multiply it by the radius, okay? So let's do that. So we have 4 pi over 1 minute times the radius. It tells us it's 150 meters, so it's 150 meters, okay? And so let me scroll down and get some room going here, okay? So 4 times 150 we know is 600. So this ends up being 600 pi meters, okay, per 1 minute. So the last thing we want to do is get this in terms of seconds, okay? And the reason I waited here is because you have to divide by 60, and 600 divided by 60 is pretty easy to do, okay? So that's why I waited. So you can multiply this now by, I want seconds in the denominator because I want it as per second, and there's 60 seconds in 1 minute. Let me slide this down. I kind of ran over a little bit. Let me slide this down, and I'll put 1 minute up here so that it will cancel. Again, you want to, and let me abbreviate this so that it's consistent, you want to put these across from each other, again, so they cancel. So this will cancel with this, and I'm just left with seconds now, right? I'll have meters per second. So 600 divided by 60 is going to give me 10. So this would be 10 pi meters per second, or you could say it's about 31.4 meters, okay, meters per second, okay? So to answer this little word problem, I'll say that Max's cart is traveling at about, again, it's an approximation, 31.4 meters per second. Okay, so Max's cart is traveling at about 31.4 meters per second. In this lesson, we want to talk about graphing sine and cosine. All right, so to start out the lesson, I'm going to talk about something called a periodic function. So when we think about sine and cosine, these guys are called a periodic function because their values repeat in a regular pattern. So to see what I mean by that, let's revisit the unit circle from the last section. So from our unit circle, what we see here is that as we travel around our unit circle, so in other words, if I start here, let's say I make a counterclockwise rotation, okay? So a positive angle measure, and I do one full rotation. Well, that's going to be an angle measure of 2 pi. We already know that, okay? But as I continue past 2 pi, so let's say I created an angle that was greater than that, so I keep going around, okay? So let's say I make an angle that's 4 pi, so 2 full rotations. What's happening is these values for sine and cosine are going to repeat themselves, okay? So anything past 2 pi. So when we talk about 2 pi for sine and cosine, this is going to be known as our period. It's the smallest possible positive value for where these function values, okay, these values for sine and cosine are going to repeat themselves, okay? Let's think about this with a simple little example. Let's say I think about this angle measure here, which is pi over 6, or 30 degrees. I know that the sine of pi over 6 is given by the y value of that point right there. Okay, so this is equal to 1/2, okay? But also, if I was to rotate around another 2 pi, okay, so another 2 pi, I'm going to get back to that same point right there, okay? So I have a coterminal angle, and my sine value is going to be the same. So in other words, if I said the sine of pi, let me use parentheses here, pi over 6 plus another full rotation would be 2 pi. Let's go ahead and write that as 12 pi over 6 so we can have a common denominator. This is going to be equal to 1/2 as well, okay? If I add these up, pi plus 12 pi is 13 pi. So this is 13 pi over 6, okay? This is 13 pi over 6. If you punch this into your calculator, you'll see that you get the same value either way. And you can keep going around another 2 pi, or you can go the other way. You can go clockwise 2 pi. So basically, as you're adding these multiples of 2 pi, you're getting these coterminal angles, and so your sine values are the same, and also your cosine values are the same. So if we go back up to our little definition of a periodic function, you see we have f of x. X is just some member of the domain. In the case of sine or cosine, it would be any real number. This is equal to f of, you have that same x value, plus n, which is some integer, times p, which is going to be our period, which in this case is going to be 2 pi, okay? So I could say something like the sine of x, and I could say really this is equal to the sine of, I'll say that same x value, plus some integer n, times the period p, which is 2 pi, okay? This is something that is very important to write down. We're going to use this not only in this section, but also when we solve trigonometric equations. So then we could say the cosine of x is equal to the cosine of, you have your same value for x, plus your n times your 2 pi, okay? In our example, we saw, let me write this off to the side, that the sine of basically the pi over 6 was equal to the sine of, we had pi over 6 again, okay? And then what we did was we added just 2 pi, right? Our n was 1. But really, you could put n times, let me scooch this down because it's going to run out of room, n times your 2 pi here, okay? So you can plug in anything for n as long as it's an integer, and this statement would be true. You would basically get 1/2 on the left and 1/2 on the right after you evaluate. Okay, before we move any further, I want to clear up something that is a common source of confusion, and that is what to do with this point right here, okay, which contains an x value and a y value when you're working with something like y equals the sine of x or y equals the cosine of x, which we're going to get to in a moment. Let me just erase this, okay, and we'll build up to what we need to do. Okay, let me actually erase this. I want to show you again where things come from, even though we talked about it in the last section. We have a unit circle here, okay, so that means the radius is 1. Okay, so this r value here, or this distance from right here to right here is 1. Okay, you can see that from here, which is the origin, 0, 0, to here, which is 1, 0, that's 1. From here to here is 1, from here to here is 1, from here to here is 1. So we see the radius is 1. Now, if I go back to my definition of cosine of theta and sine of theta, again, if I have a point on the terminal side, well, then the cosine of theta is given as x over r, and the sine of theta is given as y over r. Well, here, my r value is 1, so the cosine of theta is exactly equal to x, or the x coordinate from that point. So this is exactly equal to x. For the sine of theta, again, y over r is 1, so this guy is exactly equal to the y coordinate from that point. So it's really important to understand that when I grab this x value, it's the cosine of theta. When I grab this y value, it's the sine of theta, okay? Now we move on, and we introduced this s now instead of theta. Okay, that further complicated things. The reason we're using this is so that we can have real numbers as our domains for the trigonometric functions, right? We started to call these guys circular functions. So s here is the arc length of the intercepted angle, okay? So s is exactly equal to theta, okay? So now we can say that for this point right here, the x value is the cosine of s, okay? This arc length here. And then the sine of s is going to be y. Okay, so that's all we really need to know. When we come back to our little unit circle, if we think about something like y is equal to the sine of x, or let's say y is equal to the cosine of x, it's important to know what's going on, what you're plugging in for x, and what you expect as an output for y. We are plugging in angle measures here, typically in radians, for x, and we are getting sine values out for y. Okay, so in other words, if I look at, let's say, this point right here, I am not taking this as the x value and this is the y value. That is not how that works. I want the angle, okay, so pi over 6. In other words, let me erase this for a moment. If I said y is equal to the sine of pi over 6, what's the y value? Well, the sine of pi over 6 is given by this y value here for this point, right? The y coordinate from that point, which is 1/2. So this guy right here would be 1/2. In other words, a point would be pi over 6, comma, 1/2. Another one would be, let's say I did pi over 4, well, the sine value would be square root of 2 over 2. So another one would be pi over 4, comma, square root of 2 over 2, okay? And you can continue making points like this to sketch your graph of sine. I'm going to show you a better way in a moment, but for right now, I just want to make sure that's clear for you, okay? If I did a few with cosine, just really quickly, so y equals the cosine of x. Again, if I plugged in pi over 6, so y equals cosine of pi over 6. Well, what is the cosine of pi over 6? I'm not looking at the y value now. I'm looking at the x value for this point, okay? It's square root of 3 over 2. So this would be square root of 3 over 2. And so the ordered pair there would be pi over 6, comma, square root of 3 over 2. Okay, so it's very important that this is clear for you in terms of what you're plugging in for x and what your output is for y. Now, with that being said, let's go through and let's think about some of the basic points that you're going to get from a sine graph. Okay, so we're going to be looking at y equals the sine of x. This is a function, so you can use function notation. F of x equals sine of x. It's not a one-to-one function, but we'll talk about that later on in the course. Okay, so if we look at these y values here, we're going to be focused here, 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 and here, right? So as we start from an angle measure of 0, okay, and we go to pi over 6, pi over 4, pi over 3 to pi over 2, you'll see that the sine of x, or the y value, okay, is going to increase from 0 to 1/2, square root of 2 over 2, square root of 3 over 2 to 1, okay? Then as we go from pi over 2 to pi, this guy's going to now decrease from 1 down to 0, okay? So you're going to go to square root of 3 over 2 again, square root of 2 over 2, and then 1/2, and then back to 0, okay? Then as we get into our quadrant 3 and our quadrant 4, remember sine is going to be negative. So from pi down to 3 pi over 2, we're going to be decreasing from 0 down to negative 1, okay? So you can go to negative 1/2, negative square root of 2 over 2, and negative square root of 3 over 2. Finally, you get to negative 1. And then lastly, from 3 pi over 2 up to 2 pi, so up to 1 full rotation, we're going to increase from this negative 1 back to this 0, right? So you go in negative square root of 3 over 2, negative square root of 2 over 2, and then finally negative 1/2. Now, you do not need all of these values as ordered pairs. You can just start off by taking the first few guys that you get in the first quadrant, along with your quadrantal angles, okay? And that's basically enough to get started. After that, I'll show you that you really only need 5 key x values to draw this guy over one period. You're going to draw a wave-like function, okay? So if we start with 0, that's our angle measure, the y value is 0. Then pi over 6, you get a half. Then if we do pi over 4, you get square root of 2 over 2. Then if you do pi over 3, you're going to get square root of 3 over 2. Then if you do pi over 2, you get 1. Pi, you get 0. 3 pi over 2, you get -1. And 2 pi, which is one full rotation, you are back to 0. All right, so now that we have some basic points, let's go through and draw our first graph of, I'm going to go ahead and label this as f of x is equal to the sine of x. I'm specifically going to say here, because this is over one period, so from 0 to 2 pi, so one rotation, I'm going to say that x is greater than or equal to 0 and less than or equal to 2 pi. I'll show you in a minute that this continues to the right and to the left forever, okay? So what we've done here, we've put a little bit of detail into this, more detail than you really need. You'll see I have these notches that are going to be in increments of pi over 6. We're going to start out with an angle measure of 0, okay? Again, the sine of 0 is 0, so your x value is 0, your y value is 0, okay? Then as you get to pi over 6, what's going to happen is your sine of pi over 6 is a half. So you can say this right here is a half, okay? And you could label that, this is pi over 6, comma 1/2, and I'm trying to make that a little bit better here, okay? Then as you continue, then you have your pi over 3, and the sine value for that is going to be square root of 3 over 2. So this right here would be your pi over 3 and then square root of 3 over 2, okay? And then at pi over 2, you get to the maximum y value, which is 1, okay? So that's right there. Then you start decreasing again. Remember, after pi over 2, you're coming back down to a y value of 0. So you're decreasing. So now this is your maximum. Then you're going to come back to your square root of 3 over 2 in terms of your y value. You're going to come back to your 1/2 in terms of your y value. And then you come back to 0 or an x-intercept when you get pi, okay? So then as we continue from pi to 3 pi over 2, we are decreasing from 0 down to -1, which is the minimum, okay, for the y value. Then as we go from 3 pi over 2 back to 2 pi, back to one full rotation, we're going back to 0. This just goes directly in line with what we were doing on the unit circle. Now, when you graph these guys, let me erase all of this. You really do not need all of this detail, okay? I put some notches here in terms of pi over 6. Typically, if you're asked to graph something over one period, you're going to make 5 notches for the 5 key x values, okay? You're going to have a starting point, you're going to have a quarter point. Let me mark these off. So you have a starting point, a quarter way point, a middle point, a 3/4 way point, and then an ending point, okay? For the basic sine graph, it's really easy because these key x values are going to be your quadrantal angles, right? So this is, if you think about it in degrees, if that's easy to remember, this is 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then 360 degrees, okay? So very easy to get those 5 values. I'm going to talk about in a moment splitting up the period into fourths, but I'll get to that in a moment. So let's go down here, and I want to think about what happens when we extend this to the right and to the left. Well, again, if I start off here with my x value of 0, let me write this out. So now this is f of x equals sine of x. Okay, no restriction. We're going all the way through. One full rotation or one cycle would be, I would go up to 1, I would go back through my x-intercept, down to the minimum, and then back up to my x-intercept. Okay, so this is one cycle or one rotation on the unit circle. Every other part of that graph is just made up of repetitions of this. Okay, you can see this is called a sine wave. Okay, so when you graph this guy, you're going to have your 5 key points. So 1, 2, 3, 4, 5, given by the 5 x values, which I'll talk about in a moment, and then the corresponding y values, obviously. And then you're going to sketch that wave and just continue that wave indefinitely to the right and to the left based on what your teacher says. Okay, you've seen that I've marked this off in increments of 2 pi, so that's your period. And another way we want to think about this, if you're going this way, okay, think about what a negative angle measure means. This graph is in terms of pi over 2, right? Those are the notches. So this is negative pi over 2. This is negative pi. This is negative 3 pi over 2. Remember what it means to have a negative angle. It means I'm rotating clockwise. If I go back to the unit circle, if I start here and I rotate this way, okay, I'm going to end up with negative pi over 2, which is coterminal with 3 pi over 2. So the sine value is negative 1. Then as I keep going, I'm going to end up with a negative pi. The sine value is 0, right? This is coterminal with pi. Then as I go and I continue, then I'm going to end up with negative 3 pi over 2. This is coterminal with pi over 2. So the sine value here is going to be 1. And then finally, as I make my full rotation going clockwise now, okay, I'm going to end up with negative 2 pi. And my sine value there is going to be 0 once again. So when you return, if you think about this, again, as we get to an x value of negative pi over 2, our y value is going to be negative 1. As we get to an x value of negative pi, our y value is going to be 0. As we get to an x value of negative 3 pi over 2, our y value is going to be 1. As we get to an x value of negative 2 pi, a full rotation, we're right back to 0. We're hitting the x-intercept. Now, here are a few things that you absolutely need to know when you work with the sine function. First off, this guy is continuous across its entire domain. The domain is a set of real numbers, okay? So that means you can plug in any real number you want, and you'll get a corresponding y value. It also means that when I say continuous, you can graph this guy without ever lifting your pencil. There's no holes, no gaps, nothing like that, okay? Additionally, when we think about the x-intercepts, so you think about here and here and here and here and here and here and here, these are of the form, let me write this out, the x-intercepts are of the form n times pi, okay? Where n is some integer. So you can think about this as being 0 times pi, that's 0, then 1 times pi is pi, then you'd have 2 pi, then 3 pi, then 4 pi, work going negative, so you'd have basically negative pi and negative 2 pi, so on and so forth. Now your range for sine and also for cosine is from negative 1 to positive 1. So the minimum y value would be negative 1, and that's included, and the maximum y value is positive 1, and that's included. So we can say our range, and let me put the e there, forgot that. So our range is going to be from negative 1 to positive 1, like that. Now, the last thing I want to talk about is that this graph is symmetric with respect to the origin. So when this happens, we call this an odd function. So let me go back to the unit circle, and let me demonstrate this real quick. For an odd function, f of negative x is equal to the negative of f of x. Now, this is going to come up in our section on identities. We're going to need this, what we call negative angle identity, to rewrite things. But for right now, I just want you to understand this concept. If I have the sine of negative x, let me put this in parentheses, this is equal to the negative of the sine of x, okay? Let's just go back to this pi over 6. If I do the sine of, let's say, negative pi over 6, what would that be? Well, that would be me starting here and rotating clockwise, okay, to right there. It's coterminal with 11 pi over 6, so the y value for that point would be negative 1/2. So this is negative 1/2, let me write that. This is equal to the negative of the sine of x, okay? I have a negative x, I want just x, so the negative of the sine of pi over 6. So the sine of pi over 6 is given by this y value here. So this is going to be the negative of sine of pi over 6, which is going to be negative 1/2 as well. Okay, let's move on now and talk about graphing variations of the sine graph. I'm going to go through all the different transformations that you're going to come across. We're going to start off with the vertical stretch or vertical compression, okay? And in order to graph these variations by hand, what you want to have are the x-intercepts. You want to have your maximum point and then your minimum point, okay, if you're looking at one period, okay? So when we look at one period or one cycle, you think about your x-intercepts for your basic sine graph. Let me write this out again. So f of x is equal to the sine of x, or x is greater than or equal to 0 and less than or equal to 2 pi. Your x-intercepts occur at the beginning, the middle, and the end of your period, okay? So 0, pi, 2 pi, okay? Then in terms of your maximum and your maximum is going to occur at a quarter way through the period, okay? So 2 pi divided by 4, or 2 pi times a fourth, that's going to give you pi over 2. And then your minimum is going to occur at 3/4 way through your period. So 3/4 times 2 pi will give you your 3 pi over 2, okay? So what you want to do to get these x values in any situation is you want to set yourself up a little table, okay, or you could say just some scratch work, and you want to first divide your period by 4, okay? So with the basic sine function, the period is 2 pi, okay? We're going to divide this by 4, so we cancel this with this and get a 2. So basically you have your pi over 2, okay? So you're going to start off where your cycle begins. For the basic sine function, it's going to start at 0. Okay, so let me put 0 here. And then what you're going to do is you're going to just keep adding pi over 2 to the previous value. So here, x sub 2, or the second x value, is this x sub 1, which is 0, plus your pi over 2, so that's pi over 2, okay? And then here it's pi over 2 plus pi over 2, which is pi, and then plus pi over 2 again, which is going to be 3 pi over 2, and then plus pi over 2 again, which is going to give me back to 2 pi, okay? Typically, as a check, a lot of books will say, take your ending value minus your beginning value, so 2 pi minus 0. If that equals your period, you're pretty much good to go, okay? Now, that doesn't mean you didn't make some mistake in between, but at least you know that your cycle is the right length. All right, so let's start talking about some of the function transformations that we're going to see. The first type is very, very easy. This is where we have a vertical stretch or a vertical compression. You'll recall from earlier in the course, if we have something like a multiplied by f of x, basically if this a value, we'll say the absolute value of that, if that's greater than 1, you're going to have a vertical stretch. If you have the absolute value of a being greater than 0 and less than 1, now you're going to have a vertical compression, okay? So all your function values or your y values are being multiplied by this guy a here, okay? So what we see here is we have f of x is equal to a, that's multiplying the sine of x. So the original function is sine of x. A is now multiplying that. And I'm specifically going to say that a is any real number that is not 0. Okay, so some non-zero real number. So the example we start with is f of x equals 2 times the sine of x. So basically we know that since this is a 2, and the absolute value of 2 is 2, and that's greater than 1, this would be a vertical stretch, right? Because all the function values, all the y values are being multiplied by 2 when we compare it to the original function, f of x equals sine of x. And you can see this. So the x-intercepts here, here, and here, obviously the y values are 0, so those are going to stay the same because 0 times 2 is still 0. But if you look at this maximum y value of 1, okay, if you multiply that by 2, you're now at 2. Okay, 1 times 2 is 2. If you look at the minimum y value, which is negative 1, you multiply that by 2, you're down here to negative 2. Okay, so this guy has been vertically stretched by a factor of 2. Now, when we think about the period for a function of this form, it's still going to be 2 pi. Okay, so we haven't introduced any type of shift. We haven't introduced any type of horizontal stretch or compression. So the period is still 2 pi. We're still starting out with an x value of 0. So you still have the same 5 key x values at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so basically to get these points, you really just need to think about the fact that you're multiplying the y values from your original function by 2. Okay, that's all you really need to do. Now I'm going to talk about in a moment the fact that you can use this a value to find your maximum and minimum y value, but we're going to talk about that later on when we talk about the amplitude. Okay, let's look at another example. Again, I'm working with f of x is equal to a times the sine of x. Here we have f of x equals 1/2 times the sine of x. So what do you think is going to happen here? We're going to have a vertical compression. Okay, so basically all your y values now are multiplied by 1/2, and that's compressing your graph, okay? So again, you get your x values in the same way. The period has not changed, so it's still going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. That part's really easy. So the x-intercepts, the y values are always going to be 0. And then for these y values here on your new graph, again, you can just multiply the previous ones by 1/2, or you can evaluate the function there. Or again, I'll talk in a moment about how to get the minimum and maximum value. You might notice that when we had 2 times the sine of x, it was 2 and negative 2. When we just had sine of x, it was 1 and negative 1. Here we have 1/2 times the sine of x, and it's basically 1/2. I can put that in. This is 1/2. And then down here, this is negative 1/2. So you see the pattern is that your maximum and minimum is related to this right here. We'll talk more about that in a moment. All right, let's take a look at one more of these in this form. So now we're going to look at f of x equals negative 2 times the sine of x. So you actually have two different things going on. One, you have a vertical stretch of a factor of 2. And then you have that negative there that's going to cause a reflection across the x-axis. So compared with the graph of f of x equals the sine of x, basically all your y values are multiplied by negative 2. Okay, so again, you have the same period, so you have the same x-intercepts. So you can have this guy, and this guy. Those are going to be the same, right? Y values are still going to be 0. But when you look at this guy and this guy, okay, you can go from your basic sine graph and you can just multiply those y values by -2. So 1 multiplied by -2 gives you this -2. And then -1 multiplied by -2 is going to give you this +2. Okay, and if you think about this in terms of your f of x equals 2 times the sine of x, again, the negative there, if you have the negative of f of x, whatever you're working with, it's a reflection across the x-axis. So if we go back and look at this guy one more time, you can see that we have this peak here, okay, where your x value is pi over 2 and your y value is 2, okay? So this is going to be reflected across the x-axis. And so now this is going to be your minimum point, right? So at pi over 2, comma, -2. And this guy right here, which was your minimum, right, where you had 3 pi over 2, comma, -2, well, now this is going to come up and be your maximum. It's getting reflected across the x-axis. So now it would be 3 pi over 2, comma, +2. If we go back, you'll see that's exactly what we have here. Okay, so let's make a few generalizations. You should notice that this is -2 here, and the maximum is still 2, and the minimum is still -2. So what I would say here is that if you have this f of x is equal to a times the sine of x, where, again, we're going to say a is not 0, but it could be any real number you want other than that, then basically, if you think about the range, okay, and this is going to give us our maximum y and our minimum y, then what I do, I'll put some brackets here, and I'll say it's from the negative of the absolute value of a to the absolute value of a. And I'm using these square brackets here because these values are included, right? If we look at this -2 here, the absolute value of that is 2, so you'd want -2 to +2. Again, both are included. If you went back to a half, it would be -1/2 to +1/2, both are included. If you had +2, again, it would be -2 to +2, both are included. If this was 57, then it would be -57 to +57, so on and so forth. All right. The next concept I want to talk about is known as the amplitude. This is something you need to know when you work with the sine or cosine function. And it's going to be the same for the basic sine graph and also the cosine graph, which we'll talk about later on. So over one period, let me write this out. So f of x equals the sine of x. Again, x is greater than or equal to 0 and less than or equal to 2 pi. So we're looking at this right now. And basically, you'll see that I've written that the amplitude is 1. So what does that mean and where does it come from? Well, basically, when you think about the amplitude, you're thinking about something that describes the height of the graph both above and below your horizontal line that passes through the middle of the graph. So for the basic sine or cosine function, that's going to be your x-axis, okay? That's going to be your x-axis. So it would be the line y equals 0, okay? So from this guy right here to this guy right here, your minimum y value is -1. It's a distance of 1. Or you could say from right here to up here, that's a distance of 1 as well, however you want to draw it. Now, the formula we use is basically to grab the a value and take the absolute value of that, and that's going to be your amplitude. Here, you can think about your a value being 1, okay? So the absolute value of 1 is 1, so the amplitude is 1. A more precise definition comes from the fact that you're taking half of the difference between the maximum and minimum values. So if you take your maximum, which is 1, you subtract away your minimum, which is -1, minus a negative is plus a positive, so this becomes 1 plus 1, which is 2. If you took half of that, you're right back to 1. If you want to look at another example of this, again, we've been working with f of x equals 2 times the sine of x. Again, just take this number out in front, which in this case is a 2. Take the absolute value of it. So if it was 2 or -2, the amplitude is just going to be that number. And again, you can see the distance from this guy right here down to your minimum, okay, that's going to be a distance of 2 units. And again, you could just go 2 minus a -2. That's going to be +4. You half that and you're back to 2, okay? If you wanted a more generic formula, again, you can go f of x equals a times the sine of x, where a is not 0. And you could say, okay, well, I know the range from earlier is from the negative of the absolute value of a to the absolute value of a, okay? So that tells me that the minimum y value would be the negative of the absolute value of a. So let's just go ahead and say the maximum y value is going to be the absolute value of a. So a minus the negative a is going to be 2a, okay? So this is 2a, and if I half that, I just get a. And of course, we're going to use absolute value bars just to account for the fact that this guy could be positive, it could be negative. So we want to account for that, so we use absolute value bars. So your amplitude, I'm just going to put AMP, is always found as the absolute value of a, this guy out in front. All right, what I want to do is consider when the period for sine or cosine is not 2 pi. I'm going to work with the sine function, but this works the same for the cosine function. So we have something like f of x equals a times the sine of, now we have bx, and I'm specifically going to work with b being greater than 0 in our examples today. You might get examples where b is less than 0. I'll talk about how to deal with that, but we're not going to get to that scenario until the next chapter, okay? So I'm going to put a comma here. I'm also going to say that a is not equal to 0. So any real number that's not 0. So in order to consider how this is going to change our graph and how this is going to change our period, I want you to first consider that if b is 1, that's what we've been working with. So f of x is equal to a multiplied by the sine of x. This has a default period. So this has a default period of 2 pi, okay? Now, where does that come from? Well, it comes from the fact that as you rotate on your unit circle, starting at an angle measure of 0 in terms of radians, around one rotation going counterclockwise, to complete that rotation, you end up with an angle measure of 2 pi, okay? So that's one cycle. So we would say x is going to be greater than or equal to 0 and less than or equal to 2 pi, okay? So this is what happens as long as you have this format. It does not matter what the value for a is. Remember, this is affecting us with a vertical stretch or vertical compression. This could be negative, it could be positive, it could be a fraction. It doesn't matter. It will not change your period. Now, when you consider that you're throwing this b into the mix, now something is multiplying x, okay? So it's changing the speed at which you're going through one cycle, okay? So you can throw this into your inequality, okay? And you can basically say that I'm going to put a bx inside of here because my function is going to complete one cycle as bx now increases from 0 to 2 pi. So this might give you a horizontal stretch or horizontal compression. Okay, it's going to change the speed at which you complete one cycle. And basically, to figure out what your period is, you're just going to divide everything here by b. Okay, you're going to solve this for x. 0 divided by b, well, we know that b is not 0, so this would be 0. Okay, so let me write 0 here. This is less than or equal to, well, the b's would just cancel out. B divided by b is 1, so this is just x. And then this is less than or equal to your 2 pi over b. Okay, so we don't have any horizontal or vertical shifts going on. Your starting point for the cycle, okay, would still be 0 for the x value. And now your ending point for the cycle would be 2 pi over b, okay? So we'll update the period and just put 2 pi over b, okay, like that. And this is what you want to use as a general formula. Okay, let me get rid of this. And I want to talk about some other things. First and foremost, if you are in this section in your textbook and they are giving you problems where b is negative, you can just use the absolute value bars for right now. When we get to the next section, I'll show you how to rewrite this based on the fact that sine is an odd function and cosine is an even function to where b is always greater than 0. Okay, but for right now, you can use the absolute value bars to get your period. Now, what I said earlier was that this would create a horizontal stretch or a horizontal compression. Now, where is that coming from? Let's think about a few basic examples. Let's say I said I had something like f of x is equal to, forget about the a, we'll just keep that as 1 each time. I'll say the sine of 2x. Well, let's first think about the period. So the period, okay, would be what? Well, I would have 2 pi over my b value. This is my b value, it's the coefficient of x. So 2 pi over 2, well, these are going to divide out, it's just pi. So if I think about this, it's completing a cycle, okay, starting with an x value of 0 and ending with an x value of pi, versus normally starting with an x value of 0 and ending with an x value of 2 pi. So it basically did it in half the time, right? So this is going to compress our graph horizontally, okay? So basically you can think about the fact that if your b is greater than 1, it is increasing the speed at which this bx here is going from 0 to 2 pi, okay? So obviously that is giving me a horizontal compression by a factor of 1 over b, okay? So this is horizontally compressed by a factor of 1 over b. Let me erase this and let's talk about the next situation. So if this was a value between 0 and 1, so a fractional value, now it's slowing it down, okay? So I'm going to be horizontally stretched. So let's say we looked at something like f of x is equal to, let's just do, I'm going to keep my a value as 1, so I'll do sine of 1/2 times x. Well, basically this is going to stretch me out, okay, by a factor of 1 over, you would take this 1/2 here, okay, so you're going to flip this, and this is going to be 2. Okay, so it's going to stretch me out by a factor of 2. Again, to think about this with the period, your period is always going to be, and I probably didn't write that correctly, so let me put this back in here. So the period would be 2 pi over b. Now, if I'm dividing by a half, I might as well just multiply by 2. So this is just going to be 4 pi, okay? So before, it went from 0 to 2 pi. Now it's going from 0 to 4 pi. So that is stretching the graph horizontally, right? It's taking twice as long. So let's look at a simple little diagram here. I think this will make a little bit of sense for you. So we have f of x equals a times the sine of bx. Again, we don't have any vertical or horizontal shifts, so the starting x value for your cycle is going to be at 0, and then you would add quarter periods, okay, to get these other notches. So you have your 2 pi over b, you'd multiply by a fourth to get your quarter periods, so you can cancel this with this, okay, and basically it's going to be pi over 2b, okay, that's what you're going to be adding each time. So plus pi over 2b, plus pi over 2b, plus pi over 2b, plus pi over 2b. You're still going to have your same 3 x-intercepts, okay? And essentially, you're going to have your maximum and your minimum, and you can get those from your amplitude, which is the absolute value of a right there, okay? Your maximum is going to occur at the absolute value of that guy, and then the minimum is going to occur at the negative of the absolute value of that guy. All right, let's look at 2 examples here real quick. I'll give you one where there's a horizontal compression, and then I'll give you one where there's a horizontal stretch. So we have f of x equals 3 times the sine of 2x. So the first thing I'd like to do if you're going to graph this, find your amplitude, okay? This is going to help you to figure out what's the maximum and the minimum. So this guy, again, if this is 3, it's always the absolute value of that number, so it's going to be 3, okay? Then find your period. So what is the period here? It's 2 pi over b. In this case, your b value is 2, so 2 pi over 2. So this is just going to be pi, okay? So we know because this guy right here, this 2 is greater than 1, we're going to have a horizontal compression by a factor of 1 over that number, so by a factor of 1/2. And you can see our starting x value is 0, our ending value is pi, so this is being completed in terms of one cycle in half the time, okay? So once you have those two things, you're going to go through and add these quarter periods. Let me erase this real quick and just put pi here, okay? So a quarter period would be this guy divided by 4, so it's pi over 4, okay? So we don't have any shifts yet, so we're starting with an x value of 0, then you add pi over 4, 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 right? So really easy. And you can see that pi minus 0, okay, gets you back to pi, which is your period. That's always something you check. I know it's not that important here, but when you get into things like a phase shift, which we'll talk about here shortly, it's going to be important to do that, okay? So you have pi over 4, you have pi over 2, 3 pi over 4, and then pi, okay? So you know that at the beginning, the middle, and the end, you have your x-intercepts. So the y value is already figured out for you. It's going to be 0. When you get to a quarter of the way through, and you get to 3/4 of the way through, you know that you're going to be at your maximum for a quarter of the way through, and your minimum for 3/4 of the way through. And again, from your amplitude, you know that's 3. So the maximum's at 3. Okay, that's your y value. And your minimum is at -3. Okay, so that's enough to get you the 5 key points for this sine graph here. And then just connect the points with a smooth sine wave. That's all you need to do. All right, let's look at an example now where we're going to have a horizontal stretch. So we're going to have f of x equals 3 times the sine of x over 3. And you might want to rewrite this. I'm going to go f of x is equal to, I'll put my 3 times my sine of, let me make that sign a little bit better. My sine of, instead of x over 3, I'm going to put 1/3 being multiplied by x like this. That way it's crystal clear that the b value here is 1/3. Okay, so let's start off by thinking about our amplitude. So I'm going to put AMP for amplitude. Obviously, it's just the absolute value of this number. So again, it's just going to be 3. Okay, so that tells me the maximum and the minimum, it's going to be 3 and -3, right? 3 for the maximum y value, and then -3 for the minimum y value. Okay, now when we think about our period here, so when we think about our period, we're going to have 2 pi over this b. So 2 pi divided by 1/3. Basically, you're going to flip that fraction, okay, and you're going to have 3 over 1, and you're going to multiply that by 2 pi. So the period here is going to be 6 pi, okay? So now if we think about one cycle, now starting from this x value of 0 out to this x value of 6 pi. So that's going to be one cycle for us. And essentially, we can see that it takes longer to go through this cycle, right? Instead of 0 to 2 pi, now it's 0 to 6 pi. So what's happening is this is going to be a horizontal stretch of the graph, okay? By a factor, it's always by a factor of 1 over b. Here, b is 1/3, so 1 over 1/3 is equal to 3, okay? So horizontally stretched by a factor of 3. Now, when we talk about sketching the graph of this guy, really all you need to do is get your key x values, okay? So you know this first one is going to be at 0, and you know the y value there is going to be 0. So this is 0, 0. That's pretty easy to get. From there, you want to add quarter periods, right? So you're going to go 6 pi over 4. If I divide 6 by 2, I get 3. So let me write this as a 3. If I divide 4 by 2, I get 2. So 3 pi over 2 is what I'm adding each time. So basically this notch right here would be an x value of 3 pi over 2. So this point up here would be 3 pi over 2. And then I'm going to be at the maximum, which is 3, okay? So always, when this guy is positive, I don't have any kind of reflection or anything like that, where we saw earlier we would reflect across the x-axis if this was a negative 3. I know that a quarter way through, I'm going to be at the maximum, okay, because this is positive 3. Now, halfway through, right here, I'm going to be back to my x-intercept. So to get that, I'm just going to add another 3 pi over 2 to my 3 pi over 2. That would give me 3 pi, right? So this point right here would be 3 pi, comma, 0. Okay, it's another x-intercept. Then I'm going to add another 3 pi over 2 to this. So that's going to give me 9 pi over 2. Okay, so that's going to be my guy right here. So this point right here would be 9 pi over 2. And then comma, you're going to be at your minimum. Here, that would be negative 3. So again, as long as this is positive here, your minimum is going to occur 3/4 of the way through. Okay, again, if you get a negative here, you got to reflect across the x-axis. So you got to keep that in mind. Okay, for right now, this guy is positive, so it's pretty easy. Then you add another 3 pi over 2 to this 9 pi over 2. And you're going to get your final x value of 6 pi. And of course, this is another x-intercept. So this is 6 pi, comma, 0. Okay, so once you get these 5 key points, this is enough to sketch one period of any sine function. So again, you're just going to connect the points with a smooth sine wave. All right, so we have 2 transformations left that we want to talk about. One is going to be a horizontal shift, so either shifting to the left or the right. When we talk about this with the circular functions like sine or cosine, this is called a phase shift. We also want to talk about a vertical shift, so shifting up or down. That's a lot easier to deal with, so we'll deal with that in a moment, okay? So right now we're going to look at f of x equals the a times the sine of. You're going to have this bx minus c inside of parentheses. And for right now, we're going to work with examples where b is greater than 0, just to keep things simple. Again, as we get into the next chapter, I'll talk about what to do when b is less than 0. And also what I'm going to do here is I'm going to say that a is not equal to 0. That should be obvious, but I want to list that as a restriction just so it's clear, okay? Now, when we talk about the phase shift, I want to first go back to something we learned a long time ago, just to jog your memory. So you know if you have something like f of x is equal to, let's say, the square root of x, and you compare that to g of x, which is equal to the square root of, let's go x minus 2, let's go h of x, let's say this is the square root of x plus 2, okay? Remember, when things are happening inside the function, it's a little bit counterintuitive, right? When you see x values, you're thinking horizontal axis, so I'm moving left or right. When you see this minus 2, most people assume that means that you have a shift based on this original graph, f of x equals square root of x, that you're going to go 2 units to the left. But in fact, it's the opposite. This guy is going to shift, this would shift 2 units to the right, okay? Now, what causes that? Well, you have to think about the fact that to undo what's being done to x, we've got to add 2, right? That gets me back to where I was. In other words, one ordered pair, let's say 0, 0, that's on this guy. To get the same y value for this guy, the x value has to be 2 units larger. So it would have to be 2, 0, okay? If you wanted to do another one, let's say you did for this guy, something like 9, 3, okay? For this guy, again, the x value has to be 2 units larger. So now it would have to be 11, 3, okay? Because you've got to go 11 minus 2 to get to 9, and then square root of 9 would get you that 3. Here it's just square root of 9, which is 3. If you look at this guy, again, what's being done? I'm adding 2. So to undo that, I've got to subtract 2. So that means I'm shifting 2 units to the left. So I'm going to, let me change my marker here. I'm going to shift 2 units left. Okay, so you got to keep that straight in your mind. It's the opposite of what you think, right? You got to undo what's being done to x. Now, let me erase this. And what I'm going to do is I'm going to write this in a different way, okay? So I'm going to write f of x is equal to a times the sine of, I'm going to factor this b out. Now you might be saying, well, there's no b over here, so how are you going to do that? all you need to do if you want to factor that out is basically divide each term by b. So in other words, I can put a b out here, and then inside the parentheses, I can go ahead and say, well, bx divided by b is x, and then minus the c divided by b would be c over b, okay? So this is going to make your shift a lot more clear. You can do it from this form if you want. Most people do, but I advise if you're having trouble with this to write it like this. I can also say that a is not equal to 0, and I can say that b is greater than 0 for our examples. And you might want to make this crystal clear and put some brackets here. They're not needed, but that makes it a little bit cleaner, okay? So if I look at it in this form, I know that if c is positive and b is positive, that basically I'm subtracting away a positive number, okay? And I'm going to be shifting to the right by c over b units, okay? It's very, very simple. If, for example, this was a negative c, I know b is positive because I've made it that way, well, then you have minus a negative, which is plus a positive, right? So I could really write this as plus c over b. In this case, I'm going to shift to the left, okay, by c over b units. Or you could say, really to make that crystal clear, since I said that c was negative, by the absolute value of c over b units, okay, to make that crystal clear. Let's put this back to this original form. Now, if you want to work with it in this form, it's really the same thing, okay? All you would do is start off with bx minus c, and you could set that equal to 0, and you could say, well, how do I undo what's being done to x? Well, what I could do is I could add c to both sides, okay? Cancel that, and say I have bx is equal to c, divide both sides by b, and I'll say I have x is equal to c over b. So that's going to be your phase shift, okay? Again, dealing with whether it's going left or right is just based on the sign that you have. If b, again, is restricted to be positive, well, then if c is positive and you have it in this form, you're going to be shifting to the right by c over b units, okay? If c is negative, meaning you have plus a positive, you're going to go to the left by the absolute value of c over b units, okay? This one's a little bit tricky when you think about the signs when you're in this generic form. So let's go ahead and look at an example. I think it'll be a little bit clearer. Okay, so let's look at this f of x equals 4 times the sine of, we have the 2x minus 2 pi over 3. So if you wanted to, you could rewrite this. I'll go f of x is equal to, you'll go 4 times the sine of, I would factor out the 2, okay, and I would put that out in front. And then inside, you're going to divide everything by 2. So if I divide 2x by 2, I get x, and then minus. If I divide 2 pi over 3 by 2, it's like multiplying by a half. Basically, you would cancel that 2 out with the 2 in the denominator. So you would have your pi over 3, okay? So really, when you look at it, you can just go back to my simple example with the square root. You have this minus pi over 3. So your phase shift is just going to be pi over 3 units to the right, okay? If this was a plus here, I would be going pi over 3 units to the left, okay? That's how I would write it. It's the simplest way to do it. If you don't want to go through all this trouble of factoring it, you can always say that I want to do my phase shift as c over b, okay? So my c is going to be 2 pi over 3. Let me write this out. So my c is 2 pi over 3. And then divided by b. So I'm dividing by 2, okay? So that's like multiplying by a half. And again, this 2 would cancel with this 2, and you end up with pi over 3. And again, because this was positive here, what that means is that we're going to be shifting to the right by pi over 3 units, okay? So let me write out here that my phase shift is pi over 3, and this is to the right. So pi over 3, you can put units if you want, and you will put right, okay? So you can see that by looking at the graph. Normally we start at 0, 0. Now we've been shifted pi over 3 units to the right. So the first guy for this cycle to start it off, the x value is pi over 3, and the y value is 0. So pi over 3, comma, 0, okay? Now when we talk about the other 5 key x values, from this point, it's the exact same procedure, okay? Same song and dance. So I'm going to find my amplitude. Again, that's super easy to do. Absolute value of this number out in front. So the absolute value of 4 is 4, okay? And this is not a negative, it's a positive. So you know your maximum is going to occur at the quarter way through the period. Your minimum is going to occur at 3/4 of the way through the period. So we'll get to that in a moment. But you know basically the y value here would be 4. Let me go ahead and write it out. And the y value here would be negative 4, okay? So that's pretty easy. You also know that your y value at all your intercepts, okay, which is going to occur at the halfway point and at the ending point, is going to be 0. So that's pretty easy too. So let me go ahead and put those in. Now, how do we get these x values? How do I get this one, and this one, and this one, and this one? Again, you're just going to add quarter periods. So we first need to find the period to do that. So let's go ahead and find the period. And basically, if we look at it, we have a b value of 2. So we have 2 pi over 2, which is just going to be pi, okay? So if you wanted quarter periods, it's pi over 4. So I'm going to add increments of pi over 4, okay? And you can see I already have this listed. This is something you would have to do with either a calculator or by hand. So basically pi over 3 plus pi over 4 is going to give me this 7 pi over 12. So this is 7 pi over 12. Add pi over 4 again, and I'm going to get this 5 pi over 6. So 5 pi over 6. Add pi over 4 again, I'm going to get this 13 pi over 12. So let me write that in there. So this is going to be 13 pi over 12. And then add pi over 4 one more time, and I'm going to get to 4 pi over 3. So 4 pi over 3. Now, I talked about this earlier, and it might have not made sense at the time, but when you have a phase shift, you want to take this guy, and you want to do a little subtraction to make sure it equals the period. That way you know you didn't mess up when you were adding quarter periods, okay? So 4 pi over 3 minus pi over 3 does give me the period of pi, so I know I'm good to go, right? I have all my points, and then I can just sketch my graph by making a smooth sine wave through those points. Now, if you wanted to think about all the transformations that have occurred, some teachers will ask you for that. Basically, you can think about, okay, it's been vertically stretched by a factor of 4. It's been horizontally compressed by a factor of a half, right? So remember, it's 1 over b. Your b value here is 2, so 1 over 2 or a half, okay? This guy is basically running through a cycle in half the time. Your phase shift is going to be pi over 3 units to the right. All right, let's talk about the last graphing transformation, which is basically where we're going to shift up or down, okay? So a vertical shift. We have something like f of x equals a times the sine of bx minus c, and then plus d now. We're still going to say b is greater than 0. Again, we're going to deal with b less than 0 in the next chapter. And I'm going to specifically state that a is not allowed to be 0. This is just for clarity, okay? So here, because of this plus d, this is a vertical shift. You're going to go up by d units if d is positive. You're going to go down by the absolute value of d units if d is negative. Let's go ahead and look at an example. We have f of x equals 4. Let me write this out here. So f of x equals 4. Then multiplied by the sine of, you're going to have this 3x plus 3 pi over 4. I'm going to factor that 3 out. So inside, instead of 3x, I'm going to divide by 3. I'm going to have x, then plus. Instead of 3 pi over 4, let me write this out so nobody gets lost. I'm going to divide by 3, so that's like multiplying by a third. So you're going to see that the 3's are going to cancel, and you're going to have pi over 4 right here. Let's write that in. Close that down, okay? Let me scooch this over so everything fits. You also have this minus 1 here, so we'll put that out there. If you were to think about this, let me make that a little bit cleaner. If you were to think about this in terms of all the things that have been done based on the original sine graph that we were working with, well, you have a vertical stretch by a factor of 4, okay? You have a horizontal compression by a factor of 1/3. So 1 over b, in this case b is 3. You have a phase shift left by pi over 4 units because you have x plus pi over 4 inside here, okay? So you're going left by pi over 4 units, and then you're going down by 1 unit. That's what that negative 1 is going to do, okay? So if we think about this, we can get our amplitude. Again, we know that that is going to come from this number right here. The absolute value of 4 is 4. And normally, if we don't have a vertical shift, that's going to tell us the maximum and the minimum, right? So we would know it would be 4 and negative 4. So the range here is going to change because of this minus 1. Instead of 4 and negative 4, what you're going to have is everything shifted down by a unit. So now, instead of 4 for the maximum y value, you're going to have 3. Instead of negative 4 for the minimum y value, you're going to have negative 5. So your range is going to be from negative 5 to positive 3. Okay, so keep that in mind. Now, when you talk about your period, okay, your period, that's going to be 2 pi over b, and b is just 3, so that's pretty easy. And then you're also going to need the quarter periods, so 2 pi over 3 times a fourth. Let's go ahead and cancel this 2 with this 4 and get a 2. So your quarter periods here are going to be pi over 6. So I'm going to put quarter period is just going to be pi over 6, okay? So let's talk about how we can get this graph if you're trying to do this quickly. Remember, you start off with 0, 0 on the basic sine graph. So think about all the things that are going to be done to this guy. You're going to have a phase shift of pi over 4 units to the left. So that's going to take me this way by pi over 4 units. So that point would be here now. And then we're shifting down by 1 unit. So that point's going to be right there. Okay. So I got moved from 0, 0 to that point, which is going to be negative pi over 4, comma, the y value, instead of it being 0, right? Normally that's the x-intercept. It's been shifted down by a unit. So this is going to be negative 1. Okay. Now, as we go to the next x value, so you've got this one, which is at the quarter, this one, which is at the half, this one at the 3/4, and this one at the full period, we're just adding quarter periods, right? So we're adding pi over 6 to get to the next x value, okay? So when I add pi over 6 to negative pi over 4, I'm going to get negative pi over 12, okay? So this is negative pi over 12. How do I get my y value? Again, this is positive here, so I know at a quarter way through I'm at the maximum, and the maximum is going to be 3. Okay, so pretty easy there. Then as I go back, this would have been an x-intercept, right? But it's not. It's been shifted down by 1 unit, so I know the y value here is going to be negative 1. That's pretty obvious. And then for the x value, I just take my negative pi over 12, and again, I'm just going to add my pi over 6. Just add a quarter period, and that's going to put me at pi over 12. So this one is pi over 12 right there, okay? And then at 3/4 of the period, I know I'm going to be at my minimum, right? And the minimum is negative 5. So I'm going to put a negative 5 in there, okay? And for this guy, I just take my pi over 12, and I add another quarter period, so pi over 6, and that's going to give me this pi over 4. So this is pi over 4, comma, negative 5. Then to get my last point here in this cycle, what I would want to do is add pi over 4, and pi over 6, that's going to give me 5 pi over 12. And I know the y value, that would have been an x-intercept. It's been shifted down by a unit. So instead of 0, it's going to be negative 1. Okay, so that's how you can get those 5 points. So this one, this one, this one, this one, and this one. And so that's going to be one cycle or one period of this graph. Just connect these guys with a smooth sine wave, and you're basically good to go. If you want to go to the right or to the left, you're just making repetitions of that one cycle. All right, now that we've mastered graphing the sine function, we're going to move on now and talk about graphing the cosine function. So the reason I spent all of the lesson so far on the sine function, it's a little bit easier to start with one function, learn all of the graphing transformations, and then take that knowledge and apply it to the other one. Okay, it's the same process. So if I think about f of x is equal to the cosine of x, how will this graph be different from f of x equals the sine of x? Well, basically you take your sine graph and you do a phase shift of pi over 2 units to the left, and you're going to have your cosine graph. You'll see that in a moment. So all we really need to think about is how this guy is going to be different in terms of the 5 key x values that you pick. What are the y values there? How is that going to be different? Once you memorize that, you just take the knowledge from the sine graph that you learn, those strategies, those techniques, and you apply it to the cosine graph, and you're good to go. So I'm just going to think about these quadrantal angles. We start with an x value of 0 would produce a cosine value or a y value of 1, okay? And then as we go to pi over 2, we're decreasing, right? So we're going to end up at 0 when our x value or our angle is pi over 2. Then as we continue to pi, we're decreasing from 0 down to negative 1, okay? And then as we go from pi to 3 pi over 2, we are increasing from negative 1 up to 0, okay, so right there. And then lastly, as we go from 3 pi over 2 to our 2 pi, right, we're making one full rotation, we are increasing from 0 to 1, okay? So you can refer to this table if you want to have some notes on that. Now, when we think about this guy over one period, so f of x is equal to, I'm going to put cosine of x, I'll say that 0 is less than or equal to x, which is less than or equal to 2 pi. So this is just one period. You want to think about how these points are going to be different from the sine graph. If you memorize those differences, you're basically good to go. Your period here is the same. It's still going to be 2 pi. We should know that from the unit circle. Now you'll notice that you have a maximum here and a maximum here. And this, if I draw a line down the middle, I want you to notice that you could take this point and reflect it across this line, and you'd end up with this point. Remember, that is an even function, right? So where f of negative x is equal to f of x. We've seen this with the squaring function, right? If you saw something like f of x equals x squared, doesn't matter if I plug in a 2 there, 2 squared is 4, or a negative 2 squared is also 4, you get the same y value, okay? So cosine is going to be an even function. We'll talk more about that in a moment. Okay, so another thing you'll want to think about is the fact that with the sine graph, remember, you had 3 x-intercepts. You had an x-intercept at the beginning, the middle, and the end, okay? Here, you only have two x-intercepts, and it's going to be at the quarter of a period and 3/4 of a period, okay? And then your minimum occurs at halfway, okay? So you want to remember that you start at the maximum, you end at the maximum. Halfway through, you're at the minimum, okay? And a quarter way through and 3/4 way through, you're at the x-intercept. That's really all you need to memorize. You just take the other information from the sine graph and you're good to go. Now let's extend this to the left and right. So this is f of x equals the cosine of x. So here's going to be one period from here to here, okay? So one period. Again, this is just the sine graph that's been phase shifted to the left by pi over 2 units. Okay, that's all it really is. It's the same type of graph. Now, a couple of key things. This f of x equals the cosine of x. It's continuous across its entire domain. So just like with f of x equals the sine of x, again, the domain for each is going to be all real numbers. The period for each is going to be 2 pi. So that stuff's the same. The range is -1 to +1. That's the same. The x-intercepts, this is going to be different. So the x-intercepts is going to be of the form, you're going to have 2n plus 1 times pi over 2, okay? I should probably move this so it's a little bit more clean. Let me move this down there. And basically, n is any integer. Let me make that a little bit better, because that's a little bit bad in terms of handwriting. Let's say n was 0. 2 times 0 is 0, so you'd have 1 times pi over 2. So that's this x-intercept here, okay? If you put in a 1, you'd have 2 plus 1 is 3. 3 times pi over 2 is 3 pi over 2, so on and so forth. Now, the last thing I want to do is talk about the fact that this guy is an even function. We already saw that, right, when I basically drew a vertical line at x equals pi. But you should know that basically with cosine of x, you could say that the cosine of negative x is equal to the cosine of x. We can go back to the unit circle, and you can grab a value real quick. Let's say you grab pi over 6, and you can say the cosine of pi over 6 is equal to the cosine of negative pi over 6. Really easy to prove that. Cosine of pi over 6 is square root of 3 over 2. And the cosine of negative pi over 6, I'm just rotating clockwise now. So I'm coterminal with 11 pi over 6. So this would be square root of 3 over 2 as well. Okay? So cosine is an even function. Okay, let's take a look at one example with graphing cosine. I'm going to put all the different transformations into this guy. Again, if you can do this for sine, you can already do it for cosine. Now, what I'm going to do is rewrite this to start. You have f of x equals 3 times the cosine of 3x plus 2 pi over 3. Then you have this plus 2. So let me write f of x is equal to, I've got 3 times the cosine of, I'm going to go ahead and factor this 3 out. Again, I think this is the simplest way to identify the phase shift, but you don't need it, so it's up to you. So 3 times, inside the parentheses, divide everything by 3. 3x divided by 3 is x. Then plus, if I had 2 pi over 3, and I multiplied by a third, same thing as dividing by 3, this would be 2 pi over 9. Okay, close that down. And then don't forget your plus 2 at the end. Okay, so now that we have this set up, we can identify what's going on here. We know that this 3 out in front, the absolute value of that guy, which is just 3, is the amplitude. Okay, so that's going to be 3. Now with the normal cosine graph, just like a normal sine graph, it's going to tell you your minimum is at -3 and your maximum is at +3. But if you look at the graph that's already drawn, you see the minimum's at -1 and the maximum's at 5. So what's going on? You have this plus 2 at the end, okay, and that's giving you a vertical shift up. So instead of -3 for the minimum, you add 2 units and you get to -1. So if I think about my range, okay, the minimum is now going to be -1. The maximum, again, it would have been 3, add 2 units, now it's going to be 5. Okay, and we're going to use this in a little while when we start getting these points. Now, additionally, when I think about the period, it's going to be 2 pi divided by b. Now, b here is 3, so just 2 pi over 3. If you want the quarter periods, again, this is for us to get those x values. Well, it's just 2 pi over 3 multiplied by a fourth. So basically, this cancels with this and gives you a 2. So this is pi over 6. Okay, so we're going to have pi over 6 for the quarter periods. And then when we think about the phase shift, so let me put the phase shift in here. You have x plus 2 pi over 9. So again, if you have plus 2 pi over 9, I'm shifting to the left by 2 pi over 9 units. So that means I'm going to shift to the left by 2 pi over 9 units. Now, the last thing I want to put in here, and I'm running out of room, so let me just put it off to the side. My vertical shift, as we talked about earlier, I have a +2 here, so that's up 2 units, okay? So now that we've identified all these things from just looking at our function, we can go through and think about how our points would have moved based on the original cosine graph. So it's really, really easy, okay? Now, what I would say is that this guy, based on the original cosine graph, has been stretched vertically by a factor of 3 from that guy. It's been compressed horizontally by a factor of 1/3. It's always 1/b. B is 3. So it's been compressed horizontally by a factor of 1/3. And then we've had a phase shift of 2π/9 units left and a vertical shift up by 2 units. Okay, so that's all our different transformations. So if we go to our original cosine graph, remember, the cycle starts at the maximum. The x value is 0 and the y value is 1, okay? So based on this function here, I know I'm going to start at the maximum. The maximum is 5. So I know the y value for this first point is going to be 5. What's the x value going to be? Well, I'm just going to consider this phase shift, which is 2π/9 units left. So 2π/9 units left. So that would give me a negative 2π/9, okay? And then comma 5. So that's going to be this point right up here. Okay, that's going to be the first point we get. So this is negative. Let me put my 2π/9, comma 5. Okay, so pretty easy to get that point. Now, when you go to get the other points, what I would suggest is just getting your y values first. They're really easy to figure out. Remember, at the beginning of the period and at the end of the period, you're at the maximum. So here's your beginning and here's your end. Okay, so you're going to be at the maximum. So let me put a comma here and then put a 5. Okay, so I know the y value there is 5. I know that halfway through I'm at the minimum. The minimum is -1. We already figured that out. So that's going to be right here. Let me put a comma and then -1. At a quarter way through the period and 3/4 way through the period, you would have had an x-intercept. But because we have this +2 or this vertical shift up by 2 units, now the y-coordinate is going to be 2. Okay, so for right here, the y-coordinate is going to be 2. And for right here, the y-coordinate is going to be 2. Again, if you find this confusing what I'm doing, you can always take your x values, plug them into the function and evaluate, and you can get your y values that way. This is just quicker for me and for most people as they sketch the graph. Now, to get these 4 missing x values, you already have the first one. You're just going to add quarter periods, okay? So I'm going to add π/6 to the existing x value. So negative 2π/9 plus π/6 is going to give me negative π/18. So negative π/18. Okay, so that's going to be the x value for this point right here. Okay, so negative π/18, comma 2. Then as I get to my minimum, I add another π/6 to this negative π/18. And what I'm going to get is π/9. So this point would be π/9, comma -1. Then I add another π/6 to this π/9, and I'm going to get to 5π/18. So 5π/18, comma 2. And then lastly, I add another π/6, and I'm going to get to the x value for this point, which is going to be 4π/9. Let me make that a little bit better. Okay, let me make that a little bit better. So 4π/9, comma 5. Okay, so this would be one cycle, okay, for our graph. And again, if you want to keep going to the left or the right, you're just making repetitions of that one cycle. In this lesson, we're going to talk about graphing tangent and cotangent. All right, so in the last lesson, we talked about how to sketch the graphs for sine and cosine, and we found that the process is really not that bad. The main thing to understand when you're in this section is that you are not expected to make a perfect graph. You're just expected to know the key information and how you could sketch the graph if you had to. Generally speaking, we're always going to use computer software, either something that's online or a graphing calculator like a TI-83 to sketch our graphs. So with that being said, let's go through how to sketch the graph for tangent and cotangent. We're going to start with a different period. So basically we know that the period for sine and cosine is 2π. But when you work with tangent and cotangent, you need to know that the period is now going to be pi. That's extremely important, especially when we get to solving trigonometric equations. So something like the tangent of x is going to be equal to the tangent of x plus pi n, where n is any integer, and we would also say that x is a member of the domain. Remember that when you work with tangent, you have places where it's undefined. Then we have cotangent of x is equal to the cotangent of this x plus pi n, again, where n is any integer, and x is a member of the domain. So let me just quickly demonstrate that the period for tangent and also cotangent is going to be pi. You can show this with identities, but we haven't gotten that far yet. First off, I'm just going to pick something like pi over 6 for the angle. So this guy right there. And you know that if you want the tangent of pi over 6, you can find it as the sine of pi over 6 divided by the cosine of pi over 6. In other words, we should know that the tangent of x is equal to your sine of x over your cosine of x. So the tangent of pi over 6 is going to be equal to the sine of pi over 6, and then this would be divided by the cosine of pi over 6. So what would this be equal to? We know that the sine of pi over 6, again, that's going to be given by the y-coordinate right there, so that's 1/2. So let's write that. How do we divide fractions? We multiply by the reciprocal, so this is times. You would have the cosine of pi over 6, that's square root of 3 over 2, but you're going to find the reciprocal of that, so this is going to be times 2 over the square root of 3. And then basically the 2's are going to cancel. And let's say that this is 1 over the square root of 3. We want to rationalize the denominator here, so times the square root of 3 over the square root of 3. So this equals the square root of 3 over 3. So this is the square root of 3 over 3. Now, I want you to notice that if you add pi, or you could say if you rotate by pi, so I'm going to come over here into quadrant 3, and we're going to be at 7 pi over 6. Now, I want you to think about if I found the tangent, so the tangent of 7 pi over 6, what would I get? Well, you're going to find that you're going to get that same square root of 3 over 3. And the reason for that is you're dividing in terms of absolute values the same numbers. It's just that now you're going to be dividing a negative by a negative, which is also going to give you a positive. So in other words, this is going to turn into your sine value is negative 1/2, and then divided by your cosine value, which is negative square root of 3 over 2. We're going to, again, multiply by the reciprocal. So let's go negative. We're going to go 2 over the square root of 3. And so the negative times the negative will give you a positive. The 2's will cancel. So this would end up being 1 over the square root of 3, which we know if we rationalize the denominator, that's going to be the square root of 3 over 3. So you can see that the tangent of pi over 6 and the tangent of 7 pi over 6, that's the same. So that's one way you can demonstrate this. I'll show you with some other ones, just so you can see the stuff in quadrant 2 and 4. So that's where tangent is negative. So let's say you pick something like, let's say 2 pi over 3. So that guy right there. And that color doesn't show up so well, so let me do that like that. And again, if you add pi to this, so if you add pi, you're going to come into quadrant 4, and you're going to be at this 5 pi over 3. So it should be true that the tangent of 2 pi over 3 is equal to the tangent of 5 pi over 3, because again, I added pi. Every time I add pi, I'm coming back to the same tangent value. So let's just try that real quick. So we have the tangent of 2 pi over 3. That would be equal to the sine of 2 pi over 3, which is the square root of 3 over 2, and then divided by the cosine of 2 pi over 3, which is negative 1/2. So I'm going to multiply by the reciprocal, so times 2 over negative 1. And of course, the 2's are going to cancel, and you have square root of 3 over negative 1. Let's just say that's the negative of the square root of 3. Then if I come down here to 5 pi over 3, again, if I look for the tangent of 5 pi over 3, it's going to be the same thing. I'm going to be dividing opposites. Here it was basically a positive sine value divided by a negative cosine value. But here it's going to be a negative sine value divided by a positive cosine value. Well, we know if we have a positive divided by a negative or a negative divided by a positive, I'm going to get a negative. So that's what's happening here. So this is just going to be my negative square root of 3 over 2. That's the sine value here, divided by the cosine value, which is positive 1/2. So again, I'm going to multiply by the reciprocal, so times 2 over 1. And let's go ahead and cancel this with this. And so you get negative square root of 3. So hopefully that gives you a little bit of insight into why the period is going to be pi. All right, so what we're going to do now is just look at the basic graph for tangent. We're going to do this by grabbing some ordered pairs and just sketching this guy from negative pi over 2 to pi over 2, with both of those guys being excluded. Before I show you the graph, I want to cover a few things that basically cause a lot of confusion when you first see these graphs. The first thing is we should remember that when we see a negative angle, we're rotating clockwise. In other words, something like negative pi over 2, that means I'm starting here and I'm rotating clockwise. So it's going to be this guy right here. It would be coterminal with 3 pi over 2. So this is negative pi over 2. Now, why does it say that it's undefined here? We know that the tangent of x is equal to, we have the sine of x over the cosine of x. Well, if I want the tangent of negative pi over 2, that would be equal to the sine of negative pi over 2 over the cosine of negative pi over 2. Since this negative pi over 2 is coterminal with 3 pi over 2, we could just take the value for sine and cosine from this guy right here. And so basically, you could say that this is equal to the sine of negative pi over 2, well, that's negative 1. And then the cosine of negative pi over 2, well, that's 0. What do we know about division by 0? It's undefined. So basically, you stop at this point and you would say that this is undefined. Undefined. So this would always be true whenever the cosine value is 0. So basically, this is going to happen at pi over 2, then 3 pi over 2, then 5 pi over 2, 7 pi over 2, 9 pi over 2, so on and so forth. But also you have to consider that would happen at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, so on and so forth. So a lot of books will cover this by saying that this guy is going to be undefined at odd multiples of pi over 2. So that's a good way to remember it. You could also write it as, if you want to do it this way, you could say that it's undefined at pi over 2, so this guy right here, plus pi n, where n is any integer. So basically, if it's a positive integer, then I'm rotating counterclockwise. So let's say I add pi, that's going to put me right here at 3 pi over 2. And if I add pi again, then I'd be at 5 pi over 2, then 7 pi over 2, so on and so forth. If n was a negative integer, well then basically now I have a clockwise rotation. So let's say I subtract pi, and I rotate clockwise like this, well now I'm not at 3 pi over 2, I'm going to be at negative pi over 2. And if I do that again and subtract away another pi, well now I'm going to be at negative 3 pi over 2, and so on and so forth. So all of those places it's going to be undefined because we're going to have a cosine value of 0, and division by 0 is undefined. Now the other thing you need to think about is that this guy is going to be 0 when the sine value is 0 and the cosine value is not 0. So something like, let's say, at 0, you have a sine value of 0, and the cosine value is 1. Then at pi, you have a sine value of 0, and a cosine value of negative 1. So basically for this, you could say that the tangent value is going to be 0 at pi n, where n is any integer. In other words, you could start here, and you could add pi, and you would get to pi. You could add pi again, and you would get to 2 pi, and then 3 pi, and then 4 pi, so on and so forth. And also, if you wanted to start here and rotate clockwise, so if you wanted to subtract pi away, well now I'm going to be at negative pi. Then if I do that again, I'm going to be at negative 2 pi, then negative 3 pi, so on and so forth. So basically that's where you're going to have a tangent value of 0, or you could say where your x-intercept is going to be. And you can see on the table that we've made that we do have this 0, 0. Okay, so let's look at a basic sketch for y equals tangent of x. So just using those points that we just had in our little table. So you have something like negative pi over 3, comma, negative square root of 3. So that would be this point right here. Then you have negative pi over 4, comma, negative 1. So that'd be this point right here. So this point is actually one we're going to focus on. It'll be important for us later on. Then we have negative pi over 6, comma, negative square root of 3 over 3. So that's this point right here. Then we have our 0, 0. So that's our x-intercept. And we'll focus on that one later on. Then you have your pi over 6, comma, square root of 3 over 3. Then you have your pi over 4, comma, 1. Again, this is one we're going to focus on. And then we have our pi over 3, comma, square root of 3. So that's going to be this guy right there. So one of the things to focus on here is you do have a vertical asymptote at this negative pi over 2 and then also pi over 2. And that's being created because, again, at negative pi over 2 and pi over 2, you have division by 0, which is undefined. So we've seen this previously in our course when we look at something like y equals 1 over x. Well, we know that if you plugged in a 0 for x there, this is undefined. So if you look at the graph of that, you're going to end up with a vertical asymptote at x equals 0. So here, when you have y equals the tangent of x, which you could really write as the sine of x, so the sine of x over the cosine of x to make it more clear. Well, again, where this is 0 at negative pi over 2 or pi over 2, something like that, 3 pi over 2, 5 pi over 2, 7 pi over 2, so on and so forth, well, you're getting division by 0, so you're getting these vertical asymptotes. Now, when you think about the behavior, as this guy right here approaches pi over 2 coming from the left. So coming from the left, basically as we approach this x value of pi over 2, this guy is going to increase without bound, as they say, so approach positive infinity. So I have another little table for you. A lot of books will show this. So basically at an x value of 0, we get a y value of 0. At pi over 6, you get about 0.58. That's just approximating square root of 3 over 3. At pi over 4, you get 1. At pi over 3, you get about 1.73. That's approximating the square root of 3. And then we have 1.5 is about 14.10. 1.53 is about 24.50. 1.57 is about 1,255.77, and then this 1.5707 is about 10,381.33. And then notice that as you get really close to pi over 2, so 1.570796, you get 3,060,023.31. So you can get as close to this as you want, you just can't touch it. When you actually get to pi over 2, you're going to get undefined. But as you get closer and closer to it, this number is going to get larger and larger. So again, it's going to approach positive infinity, or what they'll say is increase without bound. Now, similarly, as you approach negative pi over 2, coming from the right, this guy is going to decrease without bound. So basically, it's going to approach negative infinity. All right, so just like we saw with graphing sine or cosine, after we did one cycle of the graph, we were able to continue that to the left or to the right as much as we wanted. So here I have y equals tangent of x. So I've extended this to the left and to the right a little bit, just so you can see a little bit more. So basically, this is what we graphed already. So from negative pi over 2 to pi over 2, we see that we have a vertical asymptote at negative pi over 2, and then also another one at pi over 2. Those are what we call consecutive vertical asymptotes. So when you graph a variation of y equals tangent of x, you're going to first find those guys. I'll tell you how to do that in a moment. And then basically you have these 3 points. So this one right here is at a quarter of the way through. And let me just label this as a for right now. So a, let's just say that's negative pi over 4, comma negative 1. That's definitely something you want to memorize. Then let's call this b. This is going to be the halfway point, or the midway as a lot of books call it. That's your x-intercept, so that's 0, 0. And then let's call this point c. So that's 3/4 of the way through. So basically that point is pi over 4, comma 1. So you can use these points to basically graph any variation of y equals tangent of x. If you want these points here or wherever it is, if you just want this one right here, remember the period for tangent is pi. So I could take the x value here. Let's just call this point d. Let's call this point e. And let's call this point f. So if I wanted those, let's just go ahead and say that for point d, well, the y value is going to be the same. All I have to do is add pi to the x value. So negative pi over 4, plus pi, so 4 pi over 4 to have a common denominator, and that's going to be 3 pi over 4. So this would be 3 pi over 4, and then comma negative 1. And then for e, I know that basically I would just take 0 and add pi, so that would be pi, comma, 0, y coordinate staying the same. And then this is going to be for f. Again, I'm just going to take this pi over 4, so pi over 4. I'm going to add pi, so 4 pi over 4, so that's 5 pi over 4. And then basically, you're going to have the same y coordinate, so it's still going to be 1. And you can basically use that process to extend the graph to the left or to the right as much as you want. All right, so just some information that you need to know. So for the tangent function, the domain contains all real numbers except odd multiples of pi over 2. Some books will write that as pi over 2 plus pi n, where n is in the integer. So basically it's just telling you things like pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. You could also have negative pi over 2, negative 3 pi over 2, so on and so forth. We have f of x is equal to tangent of x. You could also write y equals tangent of x is discontinuous at odd multiples of pi over 2. So basically we've seen that the graph contains vertical asymptotes at those values. The x-intercepts are of the form x equals pi n, where n is any integer. We know that that's because that's where the sine values are 0, and 0 divided by something that's not 0 gives you 0, so that's why that occurs. The x-intercept occurs at half of the way between consecutive vertical asymptotes. So if we're using y equals tangent of x over that interval that we talked about, so from negative pi over 2 to pi over 2, with both being excluded, that's going to occur at 0, 0. Then we have our point on the graph that's a fourth of the way between consecutive vertical asymptotes. This is going to have a y coordinate of negative 1. So again, using that example, y equals tangent of x over the interval from negative pi over 2 to pi over 2, both excluded, we have that negative pi over 4, comma negative 1, and then the point of the graph 3/4 of the way between consecutive vertical asymptotes has a y coordinate of 1. So again, using y equals tangent of x over that interval, negative pi over 2 to pi over 2, both being excluded, we have that pi over 4, comma 1. So we already know that the period is pi, and then there are no minimum or maximum values. So that's important. We saw that the range is from negative infinity to positive infinity. So that tells us that the graph has no amplitude. So that's important because you might get that on your test. It might ask you for the amplitude. Remember that when you think about the amplitude, we learned in the last lesson when we were graphing sine and cosine, that's half the difference between the maximum and minimum values. Well, here again, there are no minimum or maximum values, so you're not going to have an amplitude here. Then we can also say the graph is symmetric with respect to the origin. Remember, that tells us we have an odd function. So the tangent of negative x is equal to the negative of the tangent of x for all x in the domain. Again, f of x equals the tangent of x is an odd function. All right, let's talk about the steps involved with graphing the tangent function. So what I'm going to do is give you a simple model here. And then if we get something that's a little bit more challenging, we can just modify our steps. So the first thing is we have y equals a times the tangent of bx minus c. And we're specifically going to say here that b, which is the coefficient of x, is greater than 0. Of course, we'll see scenarios where b is negative, and I'll show you how to deal with that with identities. For right now, let's go ahead and talk about the period. So what is the period? Again, when we think about this from our sine and cosine lesson, we know that if we had something like y equals the sine of bx, well, the period here, so the period here was the standard period for sine, which is 2 pi, divided by b. Well, it's a similar thought process here. When you have y equals the tangent of x, the standard period is now pi, not 2 pi, but pi. So let me put that off to the side. So y equals the tangent of x. The period is pi. So we know that. Well, here, the period for this guy right here, because you have b that's multiplying x, it's going to be pi over b. Now, I have a little sample illustration here to go through the procedure. So basically, the first thing you're going to do, you're going to find these two consecutive vertical asymptotes. And the way you do that is you go back to, again, y equals the tangent of x. We know that we generally graph one cycle from negative pi over 2 to pi over 2, with both being excluded. So you have x equals negative pi over 2, and you have x equals pi over 2. So you could say that one cycle occurs where x is greater than negative pi over 2 and less than pi over 2. So this negative pi over 2 and pi over 2, those are consecutive vertical asymptotes. Now, we don't have an argument of x, we have an argument of bx minus c. So we just have to adjust this. Let me get rid of this real quick. We're going to use the same thought process, though. We're going to say that we're going to do one cycle where bx minus c is greater than negative pi over 2 and less than pi over 2. And we can find the vertical asymptotes by saying that bx minus c is equal to negative pi over 2. So that would be one of them. We'll put and bx minus c is equal to pi over 2. So that would give you this guy and this guy. So the two consecutive vertical asymptotes that you're looking for. Once you have that, you need to find these 3 points. So you're going to have one that's a quarter of the way, halfway, and 3/4 of the way. The way you do that is you find your quarter period, just like we did with sine and cosine. And so basically, if the period is pi over b, well, you can multiply that by a fourth, and you could say that the quarter period is going to be pi over 4b. So you take your leftmost vertical asymptote, so that's x equals some number. You take that value and you add pi over 4b to that, and you're going to get the x value for the quarter of the way point. Then you add the quarter period, you get the halfway point. Then you add the quarter period, you get the 3/4 of the way point, and you could add a quarter period to get the next vertical asymptote if you wanted to, but again, you should already know what that is because you already set up those two equations. So the main thing is that you just have to find the x values there. The y values are very easy to find. You can just use the fact that at a quarter of the way through, the y coordinate is negative a. So whatever this is, it's the negative of it. Halfway through, it's going to be 0, and then 3/4 of the way through is just going to be a. Again, going back to what we saw earlier when we did y equals the tangent of x, remember I told you to memorize these 3 points. You have negative pi over 4, comma, negative 1. Well, you could put a 1 here if you want for clarity. Well, it's the negative of 1. That's how you get that y coordinate. Then you have another point, which is 0, comma, 0. That's just your x-intercept. And then you have another point, which is pi over 4, comma, positive 1. Okay, so positive 1 there. So I would just memorize those 3 points from this basic tangent function. If you do that, you're going to be good to go with any graph that you come across. All right, let's take a look at an example with the tangent function. So we have f of x equals 2, and then tangent of 2x plus 2 pi over 3, and then plus 1. So what I'm going to do is just use the procedure that we just talked about. There's alternative approaches. When I get done with this problem, I'll show you another way that you could do it. I'll just do a few points using graphing transformations only. The first thing is to think back to what we talked about a moment ago. If we're graphing something like y equals the tangent of x, generally speaking, if you're graphing that over one period, or if you say you want to graph one cycle of this guy, well, we know that we're going to do x is greater than negative pi over 2 and less than pi over 2. We know there's a vertical asymptote at negative pi over 2 and also at pi over 2 because, again, the tangent of negative pi over 2 and the tangent of pi over 2 is going to be undefined because we'd have division by 0. So what you want to do is set up an inequality here. The argument is not x like we have here. The argument is 2x plus 2 pi over 3. So this guy right here just gets plugged in for this right here. So you're going to set up the inequality. Let me get rid of this. Where you say 2x plus 2 pi over 3 is greater than negative pi over 2 and less than pi over 2. And I'm just leaving myself some space because we're going to multiply in a moment. So we're going to solve this inequality for x. So this is the goal right there. So we do have some fractions involved. I would personally like to clear those. Some people don't mind them, but I find that working with fractions is very tedious. So what I would do is look at the denominator here of 2, then you have a denominator of 3, then a denominator of 2. So the least common denominator is going to be 3 times 2 or 6. So just multiply each part here by 6, and then you can get rid of the fractions and you won't have to deal with them. So basically 6 divided by 2 would be 3. And so you'd have negative 3 pi there. So this is less than. This gets distributed to each guy. So 6 times 2x is 12x. And then plus you have 6 times 2 pi over 3. So this 6 would cancel with this 3 and give you a 2. 2 times 2 pi is 4 pi. So let me write that there. And then basically this is less than. 6 would cancel with the 2 and give me a 3. So 3 times pi is 3 pi. At this point, again, if you're trying to isolate x, what I would do is subtract 4 pi away from each part. So let me do that over here. This is going to cancel. On the left, you have a negative 4 pi minus 3 pi. That's negative 7 pi. This is less than. In the middle, you're going to have 12x, which is less than. On the right, you can have 3 pi minus 4 pi. That's negative pi. Again, if you want to isolate x in the middle, just divide each part by 12. So divide by 12, divide by 12, and divide by 12. So this right here is going to cancel. Let me slide down here a little bit. And you're going to have negative 7 pi over 12 on the left. And this is less than x, which is less than negative pi over 12. So this is telling me that my function is going to go through one cycle from negative 7 pi over 12 to negative pi over 12, where negative 7 pi over 12 and negative pi over 12 are my two consecutive vertical asymptotes. And let me come down to this page right here. Let me go back up and let's talk about the period. So what is my period? And then I'm also going to need to know what is my quarter period. So the period, again, if you're looking at y equals the tangent of x, well, the period is just going to be pi. If I change this to y equals the tangent of bx, well, now, provided that b is positive, again, if you don't have a positive b, you could just use absolute value bars, but provided that b is positive, you'd say the period is pi over b. So you're just dividing by whatever the coefficient of x is. So here, we have a coefficient of x that's 2, so the period is pi over 2, and then the quarter period is pi over 2 times a fourth, so that's going to be pi over 8. So this is pi over 8. If you want to know if you got the right period, let's come down here and paste this in and just put a little border around it. You can actually subtract. So you're going to go larger minus smaller, and you should get pi over 2. So negative pi over 12. So that's for this guy right here. And then you're going to go minus this negative 7 pi over 12. Convert this into plus. Minus a negative is plus a positive. So this becomes, you could write negative 1 there. So negative 1 pi plus 7 pi, that's going to be positive 6 pi over 12. And of course, this simplifies to pi over 2. So that confirms the period right there. So you have two consecutive vertical asymptotes. Let me put vertical asymptotes here. You have one at x equals negative 7 pi over 12. And then the other, I'll just put and here, x is equal to negative pi over 12. If you come to the graph, and I have a link for you on Desmos if you want to get something that has more detail. I have all the points labeled for you if you want to click on that. This is what we've found so far. So this is the vertical asymptote, and this is the leftmost one that we found. So x equals negative 7 pi over 12. Again, if you plug that in for x there, you're going to get undefined. So that's why you're getting a vertical asymptote there. Then this guy right here is going to be our x equals negative pi over 12. Again, if you plug that in for x there, you're going to get undefined. So you're getting this vertical asymptote here. Our next goal is to figure out what is this point, and this point. So this is the quarter of the way through, this is halfway or midway, and this is 3/4 of the way through. So let me come back and let's think about how we can use this information. So the first thing is you can find your x values by just adding quarter periods. So you can start with this one, x equals negative 7 pi over 12, add the quarter period of pi over 8, and you just keep doing that to get the next x value and the next x value and the next x value. The y values you can either plug into the function or you can use graphing transformations. So I'll show you both. Let me go ahead and grab this real quick. So you have negative 7 pi over 12 and then plus pi over 8. I'm not going to have enough room to do this on the sheet, so I'm actually going to go to another page. If you're trying to find your x value for the first quarter point, let's multiply this by 3 over 3. And let me slide this down. I'm going to multiply this by 2 over 2, just so we can have a common denominator. If you notice, you have a denominator of 12 and a denominator of 8. So this is basically 2 squared times 3. And this right here is 2 cubed. So basically the LCD is going to be 24. It's going to be 8 times 3. So this right here would turn into negative 14 pi over 24, just multiplying 2 times negative 7 pi, that's negative 14 pi, and then 2 times 12 is 24. And then plus over here, 3 times pi is 3 pi, and this is over 8 times 3, that's 24. So if you do this, negative 14 pi plus 3 pi, that's negative 11 pi, and this is over 24. Okay, let me write this right here. So for my first quarter point, the x value is negative 11 pi over 24. The quarter period, we have that listed as pi over 8, but again, we could see that we could write that as 3 pi over 24, so we have a common denominator. So go ahead and add here. So negative 11 pi over 24 plus 3 pi over 24, that would be negative 8 pi over 24. You can simplify that, but I wouldn't do it yet. Let's come down here. So this is for the halfway or midway. So basically, this is going to be negative 8 pi over 24. And if you simplify that, 24 divided by 8 is going to be 3, and 8 divided by 8 is 1. So this becomes negative pi over 3. Okay, then we want our 3/4 of the way point. So start with this. And again, just add a quarter period. So this is plus 3 pi over 24. And let me slide this down over here. So this should be negative 5 pi over 24. Just doing negative 8 pi plus 3 pi, that's negative 5 pi over the common denominator of 24. So negative 5 pi over 24. Now coming to the graph, we can see that for the first quarter point, the y value is going to be negative 1. For the halfway point, it's going to be positive 1. And then for the 3/4 of the way point, it's going to be 3. Now, how could we get that? Well, essentially, you could plug into the function or you could use graphing transformations. Let me just show you with this one right here that you could do it that way, and then I'll do the graphing transformations because it's a little bit faster. So coming back up here, you would want to say, what is f of negative 11 pi over 24? So you're just plugging in. So this equals 2 times the tangent of, you have 2 times negative 11 pi over 24. You're just plugging this right here in for x right there. So that's all you're doing. And then we'd say plus 2 pi over 3, and then plus 1. You can think about this canceling with this and giving me a 12 down here, and then I could multiply this. Let me scooch this down a little bit. I could multiply this by 4 over 4, so I have a common denominator. So this would be negative 11 pi over 12, and then plus this would be 8 pi over 12. So let me write that in. And then you would have negative 11 pi plus 8 pi, that's negative 3 pi. So you'd have negative 3 pi over 12. Negative 3 pi over 12. And of course, that's going to simplify to negative pi over 4. So negative pi over 4. We know that the tangent of negative pi over 4 is negative 1. So basically, this becomes 2 times negative 1 and then plus 1. So 2 times negative 1 is negative 2, and then negative 2 plus 1 is negative 1. So this equals negative 1. Again, if you go to the graph, you can clearly see the y-coordinate here is negative 1. So let me put negative 1 in right there. Now, what's the other way to do this? Because that's pretty slow. Well, you could have used graphing transformations. In other words, you know that on y equals the tangent of x, you have these points, which are for the quarter of the way through, again, it's negative pi over 4, comma, negative 1. And then for halfway through, it's going to be 0, comma, 0. That's your x-intercept. And then for 3/4 of the way, you're going to have pi over 4, comma, 1. Well, what's happening in terms of the vertical transformations? Well, you have this 2 out in front. That's giving me a vertical stretch by a factor of 2. And then you have this plus 1 right here, which is going to give me a shift up by 1. This is done first, and this is done second. So in other words, if I take this, let me move this down here a little bit so it fits. So if I take this right here, this y-coordinate of negative 1, and I multiply by 2 first, and then I add 1 second, well, that's negative 1 times 2, that's negative 2, and then negative 2 plus 1, that's negative 1. If I go through this one, and I go 0 times 2 plus 1, well, 0 times 2 is 0, plus 1 is 1, positive 1. And then if I look at this one, I have 1 times 2 plus 1, so 1 times 2 is 2, 2 plus 1 is going to be 3. And that's exactly what we saw. If you look at for the halfway point, well, basically the y-coordinate is 1. If you look at the 3/4 of the way point, the y-coordinate is 3. Once you know those y-coordinates, when you go to the right or to the left to extend the graph, those are always going to be the same. So for the first quarter point, it's always going to be negative 1. For the halfway point, it's always going to be positive 1. For the 3/4 of the way point, it's always going to be positive 3. So you only need to figure out the x coordinates for the vertical asymptotes and for the points that you're getting. And you can just do that by continually adding quarter periods. In other words, in terms of getting the x values, you could start here, add a quarter period, 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 and you would just keep getting to the next guy. So let's come through here and just put that this is 1, and then put that this is 3. So those are your points. Again, you can get more points if you want. That's going to be up to you. I left you a very detailed graph on Desmos where all the points are filled in. But basically, I can come through here and try to fill this in. It's going to be really tight. This point right here, let me just arrow to it and say it's negative 11 pi over 24, and then comma, negative 1. Then you have your negative pi over 3, comma, 1. So this right here is negative pi over 3, comma, positive 1. And then this one right here is negative 5 pi over 24, comma, 3. So again, you can click that link and go to Desmos and see all of these points. I've labeled them for you if you want to get more detail. All right, before I move on to the next problem, I want to show you this using only graphing transformations. This is something you should be aware of. In some cases, it's faster. You may prefer to do it this way, but generally speaking, it's very error prone because a lot of students have trouble with horizontal transformations. So things that affect the x coordinate. So let's just look at f of x equals 2 tangent of 2x plus 2 pi over 3, and then plus 1, and compare it to your f of x is equal to your tangent of x. So with this one, let me actually grab this real quick and let me come down here and paste this in. You have your basic points, which we already know at this point. Let me put a little border here. The first quarter, so basically that's going to be negative pi over 4, comma, negative 1. You have your halfway, that's going to be 0, comma, 0. And then you have your 3/4, and basically that's going to be pi over 4, comma, 1. So you think about the transformation, so you're going to have a new x-coordinate and a new y-coordinate. Of course, you also have the asymptotes to consider. So for that, you just have to think about the x. So you'd have x is equal to negative pi over 2, and so you'd have x is equal to pi over 2. And these right here, these are the vertical asymptotes. So let's come back up, and the first thing I would do is I would factor this. So I would say f of x is equal to 2 times the tangent of, pull out that 2 there. It's just going to make the phase shift a lot easier to find. So pull that out, and then you're going to have x plus pi over 3. And basically close that down and say this is plus 1. I always like to check this. So 2 times x is 2x, and then plus 2 times pi over 3 is 2 pi over 3. So that's good to go. So here is where it starts to get a little bit confusing. You have transformations that are happening to the y, those are the vertical transformations, and you have transformations that are happening to the x, those are the horizontal transformations. The vertical transformations are very straightforward. If you have something like a times, let's say, f of x plus b, so let's say g of x is equal to this, we already know that basically this right here is a vertical stretch if a is greater than 1, and it's a vertical compression, or sometimes you'll say a vertical shrink if a is between 0 and 1. Then for this one right here, this b, this is giving me a shift up if b is positive and a shift down if b is negative. So hopefully you know that already. And in terms of the order, we follow just the order of operations. You do multiplication before you do addition in the order of operations. So this is done first and this is done second. So if I look at this is done first and this is done second. So we know that for the y coordinates, again, we saw this earlier, you're going to multiply by 2 first and then you're going to add 1. So if we think about those points, and let me slide this over so this fits. When I go over here and I do my transformation, actually, let me move this to another page because I don't think it's going to fit the way that it is. Basically, you can get the y values. Again, you multiply by 2 first. So -1 times 2 is -2. Then you add 1. So -2 plus 1 is -1. And then for this one, 0 times 2 is still 0. Then you add 1, so that's 1. And then for this one, 1 times 2 is 2, plus 1, so that's 3. So that's very straightforward. It's done almost instantly. Now let's come up and let's think about the harder guy, which is going to be what's happening to the x-coordinates. Basically, what are the horizontal transformations? We know that if we have something like, let's say g of x is equal to f of, let's go ax here. This is going to be if a is greater than 1, you have a horizontal compression, or you could say a horizontal shrink. And then if a is between 0 and 1, now you're going to have that horizontal stretch. So it's always the opposite of what you think. So basically here, when you think about that 2, well, that's something that's greater than 1. So that is going to give me a horizontal compression, or you could say a horizontal shrink, however you want to say that. Now, this is the confusing part because there's different terminology. Some people will say that there's a horizontal compression by a factor of 2. If you want to say that, that's fine. Typically, I'll say it that way. Other people will say that it's been horizontally shrunk by a factor of 1/2. Whatever you want to use in terms of the terminology, just realize that you're going to either be dividing by 2 or multiplying by 1/2. Whatever you want to do there and whatever you want to say, just realize what's happening. Now, this part right here, this is your phase shift. And again, it's the opposite of what you think. If you have x plus pi over 3, that means that I want to go pi over 3 units to the left. I want to go minus pi over 3. It's always the opposite of what you see. So what you would want to do here is actually do this one first and then this one second. So why is that the case? If we were thinking about the order of operations, then you would want to do what's inside the parentheses first and then what's outside, which in this case would be multiplication, second. But again, on the inside, you have to reverse everything. This looks like I'm multiplying by 2. Well, I have to do the opposite of that. I have to divide by 2. This looks like I'm adding pi over 3. I have to do the opposite of that. I have to subtract pi over 3. And then the same thing happens with the order of operations. It has to go in reverse now. So basically, it has to be this one first and then this one second. So if we think about all the x values, the first thing you're going to do is you're going to multiply by 1/2, or again, you could divide by 2. And that's because you have to undo this part right here. You undo multiplication by 2 by dividing by 2 or multiplying by 1/2. Then the second guy here that you're going to do, you're going to subtract away pi over 3. So you can just write subtract pi over 3, or you could put add negative pi over 3. So this is what we need to do to each x to get those x coordinates. So let me come down here. We'll do it to the asymptotes first. So if you start with negative pi over 2, and you multiply by 1/2 first, that's going to be negative pi over 4. And then in step 2, you're going to take negative pi over 4. You're going to need a common denominator, so let's multiply this by 3 over 3 now. So that would be negative 3 pi over 12. So you can have negative 3 pi over 12. And you're going to subtract away pi over 3. Let's write that as 4 pi over 12, just getting a common denominator. If you do the subtraction, you're going to get negative 7 pi over 12. Notice that matches exactly what we got right here when we solve the problem in a different way. So you get x equals negative 7 pi over 12. The other guy is going to be x equals negative pi over 12. So let me erase this. And then for this one, again, all you're going to do, you're going to multiply by 1/2. So pi over 2 times 1/2, that would give me, let me actually show this. So pi over 2 times 1/2. This would be pi over 4. So that's done first. And then once you have that, you subtract away pi over 3. So you have pi over 4, and then minus pi over 3. Again, get a common denominator. This would be multiplied by 3 over 3. So this would be 3 pi over 12. Multiply this by 4 over 4. So this would be 4 pi over 12. So 3 pi minus 4 pi would be negative pi over the common denominator of 12. So negative pi over 12. Again, as I just told you, x equals negative pi over 12. That's your other vertical asymptote that we found earlier using the other approach. And we'll arrow to this. So the vertical asymptotes here, for this guy, you would have x is equal to negative 7 pi over 12, and then x is equal to, let me put and in there, negative pi over 12. So that's how you could find that using the graphing transformations only. Let me go ahead and copy this real quick, and let me come down here and paste this in. For getting the x coordinates for these 3 points, again, you just follow the same procedure. Multiply by a half, then subtract away pi over 3. Negative pi over 4 times a half, negative pi over 4 times 1/2, that's going to be negative pi over 8. So once you have that, you're then going to subtract away your pi over 3. So minus pi over 3. We need a common denominator here. That's what makes it take so long. So let's say this is negative 3 pi over 24, just multiplying this by 3 over 3. And then minus, let's multiply this by 8 over 8. So 8 pi over 24. And we get negative 11 pi over 24. And we know that's the case. So negative 11 pi over 24. Again, if you check with what we did earlier, here's negative 11 pi over 24, comma negative 1. The next one's a little bit easier because you're working with 0. So 0 times a half is still 0. So then you just need to subtract away pi over 3. So this becomes negative pi over 3. And so negative pi over 3, comma 1. Again, here's your halfway point. So negative pi over 3, comma 1. And then for the last one, you have pi over 4 times 1/2. So that's done first. So this would be pi over 8. So then we have to subtract away pi over 3 from that. So you have pi over 8 and then minus pi over 3. Again, just get a common denominator. I'm going to multiply this by 3 over 3. So this is 3 pi over 24. And then minus, you multiply this by 8 over 8. So this is 8 pi over 24. And this gives me negative 5 pi over 24. So this is negative 5 pi. Let me make this 5 better here. Over 24, comma 3. And let me show you that real quick. Here's your negative 5 pi over 24, comma 3 that we found earlier. So of course you can use this approach. Many students like it because it's a little bit faster, but you really have to understand all the different graphing transformations, particularly what's being done to x and what is the correct order. So if you have that down, then you could use this method. In some cases, it's a little bit faster. All right, let's take a look at another example with tangent. So here we have f of x equals the tangent of x over 2 minus 5 pi over 4, and then plus 1. So again, you can use the book procedure, the one that I started out with, or you could use graphing transformations. It's really up to you. I'll do this one both ways again, and then for the ones that we're going to do with cotangent, we'll have 2 examples. I'll just pretty much stick to the book method for those. So let's start off with our book method. Again, you're going to take this right here, the argument for the tangent function, and you're going to say x over 2 minus 5 pi over 4. And you're going to first say that this is greater than negative pi over 2 and less than pi over 2. So your goal is to solve for x. So we want to solve for this guy right here. So what you could do, again, if you have fractions involved, is just clear them first. It just makes your life a lot easier. And so what you see is you have a denominator of 2, 2, 4, and 2. So the least common denominator would be 4. So just multiply everything by 4 here. And let me do that like that and like that. So this 4 would cancel with this 2 and give me a 2. 2 times negative pi is negative 2 pi. So this is less than. 4 would cancel with 2 and give me 2. 2 times x is 2x. And then minus, these 4s would cancel. So you have 5 pi. And this is less than. 4 would cancel with 2 and give me 2. 2 times pi is 2 pi. Again, if I'm trying to solve for x, what do? Well, first, I would add 5 pi to each part. So let's go ahead and do that. And let me move this in a little bit more, like that. So on the left, 5 pi minus 2 pi is going to be 3 pi. So this is less than 2x. Let me show this as canceling, which is less than 2 pi plus 5 pi. That's going to be 7 pi. Again, if you want to isolate x here, just divide each part by 2. So let's go ahead and say this is divided by 2, this is divided by 2, and this is divided by 2. So this would cancel. Let me slide down here a little bit. And so now we have x is greater than 3 pi over 2 and less than 7 pi over 2. And let me come down here to a fresh page. So again, just getting the information for the consecutive vertical asymptotes. So vertical asymptotes, you're going to have x is equal to 3 pi over 2. And then you're going to have x is equal to 7 pi over 2. So if you want to come to the graph, again, I gave you a link for a more detailed version on Desmos. This is your x equals 3 pi over 2. And then this is your x equals 7 pi over 2. So far we have that. But we need these 3 points. Again, you're quarter of the way, halfway, 3/4 of the way. The first thing is we do need the period. So what is the period? Let's go back up. So this right here is x over 2. You could really write that as 1/2 times x. So you could say this is f of x is equal to the tangent of. Let me factor this because we're going to do this with all graphing transformations in a little while, so that'll already be done. Let me pull out a 1/2. So inside you'd have x minus. So then for this part right here, if you pull out a 1/2, it would be 5 pi over 2. Close that down, close this down, and then plus 1. Again, if you want to check this, 1/2 times x is 1/2 x, or x over 2 if you want to write it that way. Then you have minus and minus, and then 1/2 times 5 pi over 2 would give me 5 pi over 4. So that checks. All right, so if we look at it now, you have this 1/2 here. So the period is going to be pi divided by 1/2. So pi divided by 1/2. So you can go pi over 1 times 2 over 1, which is 2 pi. Okay, so now we know that the period is 2 pi. And then the quarter period, again, you just divide this by 4 or multiply it by a fourth. We know that 2 pi over 4 would be pi over 2. That's your quarter period. So if you want to get your x values, you're going to start with this 3 pi over 2, and then you're going to add quarter periods. Let me come down here. So let me start with 3 pi over 2, and I'm going to add pi over 2. And then basically that's going to give me 4 pi over 2. So let me write this as the quarter point, so the first quarter. You're going to have 4 pi over 2, if you want to do that now, is going to be 2 pi if you simplify. But keep it like this for adding. So for the next guy, you're going to go 4 pi over 2 plus pi over 2. That way you don't have to worry about getting a common denominator. This will give me 5 pi over 2. So for the halfway point, or the midway as a lot of books say, you have 5 pi over 2 for the x-coordinate. And then we'll do this one more time. So 5 pi over 2, and then plus pi over 2. This is going to be 6 pi over 2, which of course is 3 pi. So let's say that this is the 3/4 point, and basically the x value there would be 3 pi, just doing 6 pi divided by 2. Okay, we don't need this anymore. We have what we want. And basically all you need to do at this point is get your y coordinates. And if we go back to the graph, you can see that this right here is your first quarter, and it's going to be at 0. So you're on the x-axis. Then the midway, or the halfway point, you're going to be at +1 for the y-coordinate. And then for the 3/4 of the way, you're going to have a y-coordinate of 2. So it's going to be 0, 1, and then 2. Now, where is that coming from? Well, basically, you just have this +1 here. That's the only thing you're doing in terms of a vertical transformation. This right here is just a 1, if you want to write it. So basically all you have to do is take your normal y values, which you get -1, 0, and 1, and just move them up by 1. So in other words, instead of -1, you get 0. Instead of 0, you get 1. And instead of 1, you get 2. This is going to be 0. This is going to be +1. And then this is going to be +2. Again, that's coming from those basic points from the tangent graph. So negative pi over 4 comma -1, your y-coordinate of -1, you add 1, you get to 0. And then your halfway point is 0, 0. Your y-coordinate of 0, you add 1, you get to 1. Then your pi over 4, comma 1, you take that y-coordinate of 1, you add 1, you get to 2. So those are your points for the quarter, half, and 3/4. So you can have 2 pi, comma 0. Let me label that. So this right here is 2 pi, comma 0. Then this one right here is 5 pi over 2, comma 1. So let me label that one. This one is 5 pi over 2, comma 1. And then this one is 3 pi, comma 2. So this one is going to be 3 pi, comma 2. Now, in terms of continuing this graph to the left or to the right, remember that for these points, you're always going to have the same y value. So this one, the first quarter point, you're always going to have a y value of 0. For the halfway, you're always going to have a y-coordinate of 1. For the 3/4 way, you're always going to have a y-coordinate of 2. So that's not going to change. The only thing that's going to change is the x value. And the way you can do this is you can just constantly add if you're going to the right or subtract if you're going to the left quarter periods. That's all you really need to do to find your additional points in your additional vertical asymptotes. Okay, so one more time I'll do this with transformations only. I know a lot of people want to see this because you don't get a chance to really practice this in the book because they don't cover it in most cases. So again, when I think about this, I can put a 1 right here. So really, in terms of a stretch or compression vertically, there's none. Right? So basically you have 1 times the tangent of whatever this is, and then +1. So there's no vertical stretch or compression. This is just a 1. But you do have this +1 on the outside here, which is giving me a shift up by 1 unit. So in terms of the vertical transformations, I know that I'm just going up by 1. Again, if you want to take these right here, and let's slide this down, and compare them to the original points from y equals the tangent of x, let me do this like this. You have negative pi over 4, comma negative 1. You have 0, comma 0. And then you have pi over 4, comma 1. Well, again, all I'm doing is I'm just adding 1 to each y value. So negative 1 goes to 0. 0 goes to 1. 1 goes to 2. So we did that already, but basically that's all we're doing for the vertical transformations. Okay, let me put this right here. And now let's talk about the horizontal. Again, this is the one that's a little bit more confusing. And basically now we have the case where we have this 1/2 here. So remember, if it's between 0 and 1, now you're getting a horizontal stretch. Again, it's always the opposite of what you think. How do you undo multiplication by 1/2 or dividing by 2 if you want to think about it that way? Well, you need to multiply by 2. So the first step here, so step number 1, you're going to multiply by 2. This is going to be horizontally stretched by a factor of 2. And remember, this is going to be what you do first. Then this part right here, this is minus 5 pi over 2. So this is going to be done second. Again, it's the reverse of what you think. So since it's minus 5 pi over 2, I've got to add 5 pi over 2. So I want to shift to the right by 5 pi over 2. So let me put for number 2, this is going to be add 5 pi over 2. So again, if you always remember that, things on the inside are the reverse. So basically this is 1/2. So to undo that, I need to multiply by 2. This on the inside is minus 5 pi over 2. To undo that, I need to add 5 pi over 2. And then you even go in the reverse order. So you reverse the order of operations. Normally you do what's inside of parentheses first, and then you would multiply second. You reverse that order. So you would do this one first, you do the multiplication first, and then you do this part right here, what's inside the parentheses second. So you have to keep everything straight with the horizontal transformations. I know it gets super confusing. So if this is not something that's straight in your mind, I would just go with the other procedure. You could start off with the vertical asymptotes. So just start with your x equals negative pi over 2 and x equals, you could do pi over 2 like this. So these are your vertical asymptotes when you think about the standard y equals tangent of x that you start with. So basically I'm going to multiply by 2 first. So let's go negative pi over 2 times 2. That's going to give me negative pi. Then once I've done that, I want to add 5 pi over 2. So let me start now with negative pi. Like this, and I'm going to add 5 pi over 2. Well, let's write this as negative 2 pi over 2. And what is that going to give me? Negative 2 pi plus 5 pi, that's 3 pi, and then over the common denominator of 2. So this would go to x is equal to 3 pi over 2. Then for this one, again, you're going to multiply by 2 first. Pi over 2 times 2. Let me show this so nobody's lost. That would give you pi. And then you're going to add 5 pi over 2. So write this as 2 pi over 2. You add that together, you're going to get 7 pi over 2. So this right here is going to become x is equal to 7 pi over 2. Let me put and there. And again, if you go back and check, we found from the other method that x is equal to 3 pi over 2 and x is equal to 7 pi over 2. Those are your vertical asymptotes. Now for the other x values, again, from that first quarter point from y equals tangent of x, you have an x value of negative pi over 4. So you take negative pi over 4, you multiply by 2 first, this would cancel, that gives you 2 down there. So this would be equal to negative pi over 2. And then from there, you're going to add 5 pi over 2. So this would give me 4 pi over 2, and 4 pi over 2 is 2 pi. Again, if you look here, for the first quarter point, you have an x coordinate of 2 pi. Again, we already figured out that the y coordinate was 0. Now for the next one, you have an x coordinate of 0. So you multiply that by 2. I don't even need to show that. That's still 0. And then you add 5 pi over 2. That's going to give you 5 pi over 2. So see, our x coordinate here is 5 pi over 2 for the midway point. So we just need the last one. So you have pi over 4 for that 3/4 of the way point for the x value. And again, I'm just going to multiply by 2. So this would cancel, give me 2 down there. So now I have pi over 2. And then once I've done that, I'm going to add 5 pi over 2. And this becomes 6 pi over 2, which is 3 pi. So again, you come over here and confirm with what we already did. For the 3/4 point, you're going to get 3 pi for the x value. So that's an alternative approach if you just want to use graphing transformations. As I told you in the last example, I know a lot of students struggle with it, particularly with the horizontal transformations, because everything is the reverse, or you could say counterintuitive to what you think. All right, let's talk about the cotangent function now. So most of you know that the cotangent of x is equal to the cosine of x over the sine of x. So again, just like we saw with our tangent function, the period is pi. you could take this point right here, which is pi over 4, and the cotangent value would be 1. You're dividing square root of 2 over 2 by square root of 2 over 2. This is your cosine value, this is your sine value. The same non-zero number divided by itself would be 1. If you swing around by pi, so if you add pi, and you go to this 5 pi over 4, which is right here, again, you're dividing the same non-zero number by itself. Here you have a negative square root of 2 over 2, and here you have a negative square root of 2 over 2, so you're still going to get 1. And the same thing would be true if you looked at, let's say, 3 pi over 4, and then you looked at 7 pi over 4. Well, here, the cotangent value is negative 1 because you're dividing opposites. So if you swing around, you're going to see the cotangent value is negative 1 there as well at 7 pi over 4. So the period here is going to be pi, again, just like with tangent. When we think about the fact that cosine of x is now in the numerator, well, anywhere where the cosine value is 0, so again, we know that's at pi over 2, 3 pi over 2, 5 pi over 2, or you could go negative pi over 2, negative 3 pi over 2, basically odd multiples of pi over 2, or you can say pi over 2 plus pi n, where n is any integer. That's going to be where the x-intercepts are now. So basically, that's where this is going to be 0, and this will not be 0. So 0 divided by something that's not 0 will give you 0. Then in terms of where it's going to be undefined, well, that's going to be where the sine values are 0, because again, that gives you division by 0. So that's going to be right here at 0, then at pi, then at 2 pi, 3 pi, or you could have negative pi, negative 2 pi. So basically you would say pi n, where n is any integer. Now I have a few basic points here. So just like we saw before. So we have at 0, this guy's undefined. Again, because your sine value is 0. Then at pi over 6, you're going to get square root of 3. At pi over 4, you're going to get 1. At pi over 3, you're going to get square root of 3 over 3. At pi over 2, you're going to get 0. At 2 pi over 3, you're going to get negative square root of 3 over 3. At 3 pi over 4, you're going to get negative 1. At 5 pi over 6, you're going to get negative square root of 3. And then at pi, you're going to get undefined. So we're going to graph this over the interval from 0 to pi, with both of those being excluded, because again, at 0, it's undefined. And at pi, it's undefined. So again, we're going to get vertical asymptotes at those values. All right, let's take a look at a basic sketch of y equals the cotangent of x. Just using these points right here. Again, when you first do the graph of this, you're just going to work from 0 to pi, with both being excluded. So you can see that at an x value of 0, the y value is undefined. Because if you have cotangent of 0, you have the cosine of 0, which is 1, over the sine of 0, which is 0, and 1 divided by 0 is undefined. So that's why you get undefined. Again, as this guy approaches an x value of 0, so coming from the right, as we do this, this guy's going to increase without bound. So it's going to approach positive infinity. Then similarly, for an x value of pi, again, the cosine of pi is negative 1, and the sine of pi is 0. So if I say I want the cotangent of pi, you're setting up the fraction negative 1 over 0, that's going to be undefined. So as your x value approaches pi, coming from the left. So coming from the left, going this way, this is going to decrease without bound. We're going to approach negative infinity. Now, in terms of this stuff in between, you have pi over 6, comma square root of 3. So here's your pi over 6 for the x value. This would be square root of 3 for the y value. So this point right here is pi over 6, comma square root of 3. Then you have your pi over 4, comma 1. So this is one that you want to memorize. That's going to be your first quarter point. We're going to use that. Then you have your pi over 3, comma square root of 3 over 3. So it's going to be this guy right there. Then you have your pi over 2, comma 0. So this is your halfway point. So you need to memorize that one. Then you have your 2 pi over 3, comma negative square root of 3 over 3. So that's this point right here. Then you have your 3 pi over 4, comma negative 1. So that's going to be this point right there. That's going to be 3/4 of the way through. So that's one that you need to memorize. And then lastly, you have this 5 pi over 6, comma negative square root of 3. So that guy right there. So that's your basic points. Usually you just put this point, and this point. You make a vertical asymptote here. You don't need to make one here. You can if you want, but typically you leave that off because this is the y-axis, so you don't draw anything. And basically you just draw this to where it approaches the y-axis and doesn't touch it. And this guy is going to approach this vertical asymptote, which is x equals pi, but not touch it. So that's all you really need to do. So just like with the graph for y equals the tangent of x, when you expand this to the right or to the left, all you're doing is just copying what you previously did. In other words, we graph this right here, so from 0 to pi with both being excluded, but basically the same thing's going to happen from pi to 2 pi, 2 pi to 3 pi, or if you went this way, you can say from negative pi to 0, you could say from negative 2 pi to negative pi, so on and so forth. So you're going to have a vertical asymptote, you're going to have 3 points, vertical asymptote. So it's just that pattern over and over and over again. And these 3 points, again, the benefit to these guys right here is that basically all you need to know is what is the vertical asymptote here and what is the vertical asymptote here. So I'll show you how to get that in a moment. Once you have this one right here on the left, in this case it would be 0, you just add a quarter period. Well, a quarter of the normal period, the period for cotangent is pi, so a quarter of that is pi over 4. So I know the x value right here is pi over 4. And of course the y value is 1, we can see that. Then this one right here, again, you just add a quarter period. So pi over 4 plus pi over 4, that's 2 pi over 4, or pi over 2, and the y value is 0. Then for this one, again, I'm just adding a quarter period. Let me make that arrow better. So if you have, let's go 2 pi over 4, so we have a common denominator, plus pi over 4, that's going to be 3 pi over 4, comma, negative 1 for the y value. So the y values are things that you want to memorize because typically you're going to do this with graphing transformations. So if you know those y values, it's going to save you a lot of time. You can always plug in if you want to, but I find that to be a very tedious process. For the x values, again, all you're going to have to do is find the vertical asymptotes, figure out the period and the quarter period, and then just go through the process of adding quarter periods to get to the next x value. So I start here, add a quarter period, I get to this x value, add a quarter period, add a quarter period, add an asymptote. Add a quarter period, add a quarter period, add a quarter period, add an asymptote, so on and so forth. All right, let's talk a little bit about the cotangent function in general. So the domain contains all real numbers except for pi n, where n is any integer. So 0, pi, 2 pi, 3 pi, or even negative pi, negative 2 pi. That's where the sine value is 0, and again, division by 0 is undefined. So f of x equals cotangent of x is discontinuous at pi n, where n is any integer, and the graph contains vertical asymptotes at those values. The x-intercepts, so again, this is where the numerator would be 0, and the denominator is not 0, so these are of the form x equals pi over 2. Remember that cosine of pi over 2 is 0, and then plus pi n, where n is any integer. The x-intercept occurs at half of the way between consecutive vertical asymptotes. So if we use that basic y equals cotangent of x over the interval from 0 to pi, both being excluded, this is going to happen at pi over 2 comma 0. So you want to memorize that point. Then the point on the graph 1/4 of the way between consecutive vertical asymptotes has a y-coordinate of 1. So we saw that already. So if you're using y equals cotangent of x over the interval from 0 to pi, with both being excluded, well, you're going to have pi over 4 comma 1. Lastly, the point on the graph 3/4 of the way between consecutive vertical asymptotes has a y-coordinate of negative 1. Again, using y equals cotangent of x over the interval from 0 to pi, with both being excluded, you saw that we had 3 pi over 4 comma negative 1. So again, the period is pi. There are no minimum or maximum values. The range is from negative infinity to positive infinity, and the graph has no amplitude. So the graph is symmetric with respect to the origin. So if you did cotangent of negative x, it's equal to the negative of cotangent of x for all x in the domain. So f of x equals the cotangent of x is an odd function. So just like we saw with tangent, I gave you a little model you can use. It's not going to fit perfectly with every scenario, but we can just adjust it. So we have y equals a cotangent of bx minus c, where b is greater than 0. Again, if b is negative, which you'll see in the future, you can rewrite it using identities. If you need the period, you can just use absolute value bars. It's really not that big of a deal. It won't cause that much concern. So what we would do is say that you're going to take this bx minus c like this, and you're going to find an interval over which you're going to graph it by saying it's greater than 0 and less than pi. And that's coming from the fact that if you have y equals the cotangent of x, well, we said that we're going to go x is greater than 0 and less than pi. So again, all you're doing is you're taking this argument right here, which is the bx minus c, and you're just putting it in that place right there, and you're going to solve for x. That's all you have to do. So basically, once you've done that, you're going to find these two vertical asymptotes. So you could do it as an equation. Bx minus c is equal to 0. So that's for this one. And then bx minus c is equal to pi for this one. And then once you have that, just like with the tangent function, you can figure out what the period is. So it's just going to be pi over b. Let me write that out. So the period is just pi over b. So whatever that is, that coefficient of x, if you end up factoring that out, so if you have something like y equals a cotangent of, let's say we pull the b out because we want to use graphing transformations. Let me move this up so it fits. So then inside you would have x minus c over b, like that. Well, the period is still pi over b. So in this form, it's the coefficient of x. In this form, it's outside of the parentheses. So just keep that in mind. Now, once you have that period, you can just figure out the quarter period. So the quarter period, again, that is just pi over 4b. So just take this and multiply by 1/4. And once you have that, you take the x value here, you add a quarter period, you're going to get your x value here. So the y coordinate would just be given by a in this form. But again, if you have a shift, you have to consider that as well. You do this multiplication here first by your typical y coordinate for y equals cotangent of x, which in that case is going to be positive 1. And then once you've done that, you need to apply your shift either up or down. This 1/4 point, the y coordinate is a because again, 1 times a would be a. Then at the halfway point, the x-intercept, Well, again, I could just add a quarter period to get the x value there. And then for the y value, in this form, it's just going to be 0. But again, if you have a shift up or down, you have to consider that. Then you add another quarter period to get the x value, and then you're going to have your 3/4 point, and the y coordinate is now negative a. Because normally, if you have y equals cotangent of x, 3/4 of the way through, you have that 3 pi over 4 common negative 1. So if you take that negative 1 and you multiply by a, you get negative a. That's where that's coming from. So just keep this in mind as a general model. And with that being said, let's just go ahead and look at an example. All right, let's take a look at an example now with cotangent. So we have f of x equals the cotangent of x over 2 plus pi over 3. To start things off, I'm just going to go x over 2 plus pi over 3. So that's going to be the argument for the cotangent function there, this guy. And basically, you're going to say that this is greater than 0 and less than pi. So I'm going to get rid of these fractions here. You have a denominator of 2 and a denominator of 3. So what I would do is just multiply both sides by the LCD, which would be 6. So 0 times 6 would still be 0. Let me just show it for right now. Multiply this by 6, multiply this by 6. Let me slide this over here, and then multiply this by 6. Let me drop down a little bit. So as I just said, 0 times 6 is still 0. This is less than 6 divided by 2 would be 3, and 3 times x is 3x, and then plus 6 divided by 3 is 2. 2 times pi is 2 pi. And then this is less than 6 times pi is 6 pi. If you want to isolate x in the middle, then what you're going to do is subtract 2 pi away from each part here. Let me just put minus 2 pi here. And so this is going to cancel. We're going to have our 3x in the middle, and this is greater than negative 2 pi. And it's less than 6 pi minus 2 pi would be 4 pi. As a final step here, let me divide each part by 3 just to finish things up. So this is going to cancel. And what you're going to have is that x is greater than negative 2 pi over 3 and less than 4 pi over 3. Let me come down here and just paste this in, and I'll put a little border, and I'm going to say that's my consecutive vertical asymptotes. So vertical asymptotes, you're going to have x is equal to, you have this negative 2 pi over 3, and then let me write that better there. And let me fix this 3 here. We're going to say x is equal to 4 pi over 3. Let me show you this graphically first. So coming down to the graph, you see that you have a vertical asymptote here, and this is our x equals negative 2 pi over 3. And then you have a vertical asymptote here. This is going to be our x equals 4 pi over 3. So that we know, we need to figure out this point, and this point. So let's go back up. So what you want to do is figure out what is the period. And for this, again, let's go up here. When you look at this, you have x over 2. So you can think about that as 1/2 times x. So the standard period is pi. Again, all you're going to do is go pi over 1 divided by 1/2, or times the reciprocal of that, which is 2 over 1. So this is 2 pi for the period. Let's write the period as 2 pi. And then the quarter period, this is going to be 2 pi over 4, which is pi over 2. So again, all you have to do at this point is just go through and say, well, I'm going to go negative 2 pi over 3 plus pi over 2. So just starting at that leftmost vertical asymptote that we found. And you need a common denominator here. So let me actually write this. I'm going to multiply by 3 over 3. And I'm going to put this as, let me scooch this down a little bit so we have some room. This would be 3 pi over 6. So I have a common denominator. And this guy right here I'm going to write as negative 2 pi over 3 times 2 over 2. So this would be negative 4 pi over 6. So I'm just going to start with that. So negative 4 pi over 6, and then plus the quarter period. So that's 3 pi over 6. That's going to give you negative pi over 6. So let me write this on another page. For this one, your first quarter point, you're going to have negative pi over 6. We'll get the y values in a second. I think all of you can see that there's no vertical transformations that are applied. So you could just put 1 now if you want, but I'll just do that separately. So then we have the 1/2, and then we have the 3/4. And let's go up and get those. So I'm going to start now with the negative pi over 6. And I'm just going to keep adding quarter periods. So I'm going to add 3 pi over 6. So this gives me 2 pi over 6. 3 pi minus pi, that's 2 pi. And 2 pi over 6, you can write that as pi over 3. Let's come down here and say this is pi over 3. And then let's do that one more time. So we would want to do 2 pi over 6. So 2 pi over 6 plus the quarter period. We'll write that as 3 pi over 6. So that gives me 5 pi over 6. Let's come down and put 5 pi over 6. Now, for the y values here, again, when you look at these points, you see the y value here is 1, the y value here is 0, and the y value here is -1. That perfectly matches what we see with y equals the cotangent of x. And the reason for that is you don't have any vertical transformations here. This you could really put as a 1, so there's no vertical stretch or compression. And out here, you don't have anything. So you could put +0 to make that clear. There's no shift up or down. So you would match those y values perfectly. So for the first quarter point, you have a y value of 1. For the midway point, you have a y value of 0. And for the 3/4 of the way point, you have a y value of -1. So let's put 1 here. Let's put 0 here. And then -1 here. So we're ready to go in terms of labeling those points. You would have -pi/6, 1. So that's going to be this first point right here. So this is -pi/6, 1. That 6 could be a lot better. Then we have pi/3, 0. So this one right here, let's say that's pi/3, 0. And then this one, the 3/4 of the way, it's 5pi/6, -1. So this one, we'll say that this is 5pi/6. Let me make that 6 a lot better there. And then -1. So those are your 3 key points. Again, if you want to go to the right or to the left, you just keep adding quarter periods. So in other words, if I take this 5pi/6 and I add a quarter period, I'm going to be at 4pi/3. And you can just keep doing that to get the next point, the next point, the next point, vertical asymptote. The next point, the next point, the next point, vertical asymptote. The y values are always going to be the same. In other words, for the first quarter point, you're always going to have a y value of 1. For the halfway point or the midway point, you're always going to have a y value of 0. And then for the 3/4 of the way point, you're always going to have a y value of -1. All right, let's take a look at another one. So here we have f of x equals 1/2, and then cotangent of, we have 2x plus 2pi/3, and then +2. All right, so again, I'm just going to take the inside part here, so the argument for the cotangent function, and I'm going to start by saying 2x plus 2pi/3 is greater than 0, and it's less than pi. So we'll solve this first. And so let me slide down here just a little bit. I would get rid of this denominator of 3. So just multiply everything by 3. So you would have 0 times 3. Let me show this. So 0 times 3 is less than 2x times 3 plus 2pi/3 times 3. And this is going to be less than pi times 3. So 0 times anything is 0. So this is still 0. This is less than. 2x times 3 is 6x. And then plus, these 3's would cancel. So you have 2 pi. So which is less than 3 times pi is 3 pi. So at this point, I'm going to subtract 2 pi away from each part. Let me write that like that. And so this is going to cancel. You're going to have 6x in the middle. So this is greater than, you're going to have -2 pi. And less than 3 pi minus 2 pi is pi. To finish things up, let's divide everything by 6. And so that's going to give me this canceling in the middle. So x is greater than, if you think about 2 and 6, well, 2 divided by 2 is 1, and 6 divided by 2 is 3. So let's say this is -pi/3, and it's less than pi/6. So let's grab this. Okay, let me put that in there like that. So again, your 2 consecutive vertical asymptotes. So vertical asymptotes, you're going to have x is equal to -pi/3, and then you're going to have x is equal to pi/6. All right, so this one's a little bit busy. So again, I've given you a link on Desmos if you want to click that to get more detail. This is your vertical asymptote, which is going to be x equals -pi/3. So that guy right there. Then this is the other one. So this is the vertical asymptote. It's x equals pi/6. So we're going to be finding these 3 points right here. So let's go back to right here. If you want your period, again, it's pi, which is your standard period, divided by 2, the coefficient of x. So it would be pi/2. So let me write that the period is going to be pi/2. And then your quarter period, so this is pi/2 times 1/4. So that's pi/8. So again, all you have to do is take this -pi/3, and you're going to add a quarter period. So you're going to add pi/8. Now again, you need a common denominator. So let's just go ahead and right now multiply this by 3/3, just so that we're not struggling the whole time to get common denominators. So this right here would give me 3 pi/24. Okay, so let me adjust this. I'm going to write -pi/3 as -8 pi/24, and then I'm going to add 3 pi/24. So then for the first quarter point, the x value would be -8 pi plus 3 pi. That's -5 pi, and this is over 24. And let me put, for the first quarter point, you want -5 pi/24. Okay, so we're going to have halfway and then 3/4. We're going to figure those out right now. So let me take this, negative 5 pi over 24, and all I'm going to do is add a quarter period. So let me rewrite that. It didn't take it with it. So plus 3 pi over 24. So negative 5 pi plus 3 pi, that's going to be negative 2 pi over 24. So if you think about that, you can simplify. 24 divided by 2 is 12, and 2 divided by 2 is 1. So this would be negative pi over 12. So this is negative pi over 12. And let me get rid of that. And we only have one more to do. So let me move this over. So let me add 3 pi over 24 one more time. And so negative 2 pi plus 3 pi, that's going to be pi. And this is over 24. So this would be pi over 24. Okay, in terms of the y values, you do have to do a little bit of work here because you do have two transformations that are vertical. So let me start off with these basic points here. So on the y equals cotangent of x, you're going to have your pi over 4, comma 1. Then you're going to have pi over 2, comma 0. And then you're going to have 3 pi over 4, comma negative 1. So we're going to think about how we're going to transform here. Again, in terms of vertical, you have this guy that's done first. This is a multiplication by a half. So that's giving me, you could say, a vertical compression by a factor of 2. Or again, a lot of people like to say it as a vertical shrink by a factor of a half. It's just understanding that you're either going to divide each y value by 2 or you're going to multiply by 1/2. It's the same thing either way. It's just a matter of how you want to say it. This right here, this plus 2, that's going to shift me up by 2 units. So this is done first. This is done second. So the order does matter here. So let me write this out. We're going to, for part 1, multiply by 1/2, or again, you could divide by 2 if you want. And then for part 2, we're going to add 2. So again, this is a vertical compression by a factor of 2. Then you're going to add 2. That's shifting me up by 2 units. Okay, so we're first going to multiply 1 by a half. So 1 times 1/2 would be 1/2. Then I'm going to add 2. So you would have 1/2 plus, for 2, you could write that as 4 over 2. So this would be 5/2. So this is 5/2. All right, for this one right here, you have 0 times a half. That's still 0. Then you add 2. That's going to be 2. And then for this one, you have negative 1 times a half. That's negative 1/2. And then you add 2. So let's add 4 over 2. So this would be 3/2. So that's basically it. Just a matter of understanding those graphing transformations. Again, if you get confused by that, you can always plug in. So you could always take negative 5 pi over 24, plug into the original function, you'll get 5/2. You could plug in negative pi over 12, you'll get 2. You could plug in pi over 24, you'll get 3/2. All right, let me get rid of this. And let's just label things and we'll be done. So for this one right here, you have negative 5 pi over 24, comma 5/2. So that's going to be this one right here. So this is negative 5 pi over 24, comma 5/2. And if you look at this, it's hard to see, but this notch right here is 2. So this notch right here would be 2.5 because this notch right here is 3. And then if you look at this one right here, that's going to be negative pi over 12, comma 2. So that is negative pi over 12, comma 2. And again, this notch right here is 2. It's covered up by that point. And then if you look at this one right here, we're going to have pi over 24, comma 3/2. So this is pi over 24, comma 3/2. And again, this notch right here is 1. This notch is 2. So this is halfway. So that's 1.5 or 3/2 in terms of your y value. So you can see that does match up. Again, if you want to click the link on Desmos, you can see I've labeled all of these points for you so you can go through there and you can get some additional practice by basically just adding quarter periods to this guy. So to the x values here, you'll get your vertical asymptote, and then you're going to get the x coordinates for this guy, this guy, this guy, vertical asymptote, this guy, this guy, this guy, vertical asymptote, so on and so forth. You know the y values are always going to be the same. So for the first quarter point, you're going to have 5/2. Then for the midway point, you're going to have 2. Then for the 3/4 of the way point, you're going to have 3/2, so on and so forth. So if you want to play around with it and get some additional points going on your graph, going to the right and to the left, it'll be good to get some practice. In this lesson, we want to learn about graphing secant and cosecant. All right, before we get started with the lesson, I want to remind you that when you're in this section and you're graphing trigonometric functions, we want to understand the concept. So how could I graph the function if I wanted to? But generally speaking, if we want to get a perfect graph, we're going to use graphing software, and that's something we're going to rely on as we get out of this chapter. So don't worry too much about trying to make some perfect graph. Just do the best that you can. So when we look at this, we're going to start out by saying that in our lesson on cosine and sine, we learned that the period was 2 pi. When we think about something like the secant function, so the secant of x, this is equal to 1 over the cosine of x. So what would the period for the secant function be? Well, it's going to be 2 pi as well. The secant of x is equal to the secant of, you have this x plus 2 pi n, where x is a member of the domain and n is any integer. In other words, if I was to come to the unit circle, and let's say that I took the secant of, let's just do pi over 3, that's an easy one. So the secant of pi over 3, this would be equal to, by definition, 1 over the cosine of pi over 3. And so the cosine value for this pi over 3, again, you just look at the x-coordinate, so that's 1/2. So this would be equal to 1 over 1/2, which would be 2. If you added integer multiples of 2 pi to this angle pi over 3, so in other words, you could add 2 pi to it, 4 pi, 6 pi, or you could subtract away 2 pi, subtract away 4 pi, something like that, you're going to end up with a coterminal angle. So you're going to have the same cosine value and also the same secant value. So just to keep it simple, let's say we have the secant of, let's go pi over 3 plus 2 pi. And I would write that 2 pi as 6 pi over 3. So we have a common denominator. So 6 pi over 3. So this would be the secant of 7 pi over 3. And of course, that's going to be coterminal with pi over 3. So we know that the cosine value would be the same. So this is 1 over the cosine of 7 pi over 3, which would be equal to, again, 1 over this 1/2, which would be 2. So the period for secant is going to be 2 pi. Now let's talk about cosecant. So using a similar thought process, when we think about the cosecant of x, this is equal to 1 over the sine of x. And of course, the period of the sine function is 2 pi, so the period for the cosecant function would be 2 pi as well. So the cosecant of x is equal to the cosecant of x plus 2 pi n, where x is a member of the domain and n is any integer. All right, so we're going to start out by looking at the secant function, and we're going to do that with a table of values, and we're going to look at this over one period. So y equals the secant of x. We're going to say where x is greater than or equal to negative pi and less than or equal to pi. Now, we're not going to use this table of values approach when we graph secant in general. We'll have a different procedure for that. We're just using this to get some key points here. Now, with the other graphs for sine and cosine, and then also with tangent and cotangent, there were points that you really needed to memorize. You're not going to do that here because you're going to end up using the cosine function as a guide, and we'll get to that later on. For right now, I'm just going to focus on some things that we want to know. And so the first thing would be that you have a vertical asymptote here at negative pi over 2, and then also at pi over 2. So we want to think about where that comes from. Remember that the secant function, so the secant of x, is equal to 1 over the cosine of x. So just like we saw with the tangent function, you have your cosine function in the denominator there. So wherever the cosine values are 0, you're going to get division by 0, which is undefined, and that's giving you these vertical asymptotes. So that's going to happen at odd multiples of pi over 2. So negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. Now, another thing I want to call your attention to is that when you look at the behavior of this graph, so let's say as this guy right here goes from an x value of 0 to an x value of pi over 2. Now, it's not actually going to get to an x value of pi over 2, but you want to think about what's happening as it approaches an x value of pi over 2 coming from the left. So we would think about something like, let's say, secant of, let's just do pi over 3 again. That's an easy one. This is equal to 1 over the cosine of pi over 3, which is 1 over, again, the cosine of pi over 3 is 1/2. So notice that this value right here of 1, when I divide by 1/2, I get something bigger, I get 2. When you take 1 and you divide by something between 0 and 1, you're going to get something that's larger than 1. For example, if I did, let's say 1 divided by 1/10, I would get 10. Or let's say as another example, I did 1 divided by 1 over 100, well, that would be 100. So what's going to happen is, as the x value here gets closer and closer to pi over 2, the cosine value gets closer and closer to 0. So you can get as close to 0 as you'd like, but you can't actually touch it. So what's happening is the value is going to get really large for secant because you have that 1 divided by that number that's really, really close to 0. So this guy right here is going to increase without bound, or as they say, approach positive infinity. So let me get rid of this. We also want to think about the other side of that. So at pi, so the secant of pi is equal to 1 over the cosine of pi. So we know that the cosine of pi is -1. 1 over -1 would be -1. So here, this point would be pi, comma, -1. Now, what happens as we approach pi over 2 coming from the right? In other words, what's going on right here? And you'd see that we're decreasing without bound, so we're approaching negative infinity. Basically, what's happening is, if you think about something like, let's say, the secant of 2 pi over 3, to make it simple. So there's a pi over 3 reference angle. So we know that we're in quadrant 2. Cosine is negative. So this would be 1 over the cosine of 2 pi over 3. And this equals 1 over, now you'd have negative 1/2. And so this would be negative 2. So it's the same thing here. If you look at that point, it's going to be right there. So this would be your point, which would be 2 pi over 3, comma, negative 2. Again, as this x value gets closer and closer to pi over 2, again, coming from the right now, the cosine value is getting closer and closer to 0, but it's on the other side of 0. So it's going to be something between 0 and negative 1 now. So this guy is now going to approach negative infinity. So that's just something you really need to understand about the behavior of this graph. That's why you have this going this way. That's why you have this going this way. And that's why you have this shape right here. So once you understand that, it's basically good to go in terms of why the graph looks the way that it does. And now what I want to do is just erase some things and give ourselves a little clean slate here. And I want to go through some of these basic points. So first off, you should know this point right here, which is 0, 1. That's one that's going to be on the graph of your cosine function and your secant function. Then this one right here. This is your pi, comma, negative 1. Again, that's going to be on both. And then this one right here, that's going to be negative pi, comma, negative 1. Now, in terms of these other points, if you want to go through them in more detail, I left you a link on Desmos. So you can stop the video here, click that link, and you can look at all these points and think about where they're coming from. I'll just read through them real quick. If you have plus or minus pi over 2, again, that's where we're going to be undefined because the cosine value is 0. You have 0, 1, so that's this point right here. Then this plus or minus pi over 6, you get 2 times square root of 3 over 3. Let me actually show you that real quick so these other guys make sense. Coming back to the unit circle, again, if I asked you for the secant of pi over 6, or I asked you for the secant of negative pi over 6, you're going to get the same thing because, again, when you look at pi over 6, the cosine value is square root of 3 over 2. When I look at negative pi over 6, again, that's rotating clockwise. So that's coterminal with 11 pi over 6. Let me write out that this is negative pi over 6 here. So the cosine value is, again, square root of 3 over 2. So whether I take the secant of pi over 6 or the secant of negative pi over 6, again, I'm going to be in either quadrant 1 or quadrant 4, where cosine and secant are positive, and I have the same reference angle, so I'm going to get the same result. Let me just do this one real quick. You can get rid of this one. I'll just show you this real quick. So this would be equal to 1 over the cosine of pi over 6. And of course, this is 1 over the square root of 3 over 2. And so this would be equal to, you're just going to flip this and say this is 2 over the square root of 3, and then multiply it by the square root of 3 over the square root of 3 to rationalize the denominator. So you get 2 times the square root of 3 over 3. And again, this would be for pi over 6 or negative pi over 6. So coming back down, again, plus or minus pi over 6, you're going to get 2 times square root of 3 over 3. Plus or minus pi over 4, you're going to get square root of 2. Plus or minus pi over 3, you're going to get 2. Plus or minus 2 pi over 3, you're going to get negative 2. Plus or minus 3 pi over 4, you're going to get negative square root of 2. And then plus or minus 5 pi over 6, you're going to get negative 2 times square root of 3 over 3. And then plus or minus pi, you're going to get negative 1. You can look at that link again on Desmos if you want to go through those points. Again, we're not going to focus too much on these points. We're going to use the cosine function as a guide, so don't worry about this too much. Okay, now let's actually get into the procedure. So how do you sketch the graph of the secant function where you're going to use the cosine function as a guide? So you know how to graph the cosine function at this point. If you do it over one cycle, you would do this part right here. And I'm just going to trace over this real quick. So from 0 to 2 pi. So this is what your basic cosine function looks like. And we've graphed that a million times at this point. So you would graph that guy right there. And then what you're going to notice is that you have a shared point here. So at 0, 1, and then also here at pi, negative 1, and then also at 2 pi, 1. And I'll talk about how those come into play in a moment. But you'll notice that where you have an x-intercept, so that's right here at pi over 2 and right here at 3 pi over 2, because again, when you have the cosine of pi over 2, you get 0. When you have the cosine of 3 pi over 2, you get 0. So those are x-intercepts, and therefore, that's going to make your secant function undefined because you can't divide by 0. So you're going to get those vertical asymptotes at those values. So this is what you want to focus on here. Now, that's going to change a little bit when we get to shifting the graph up or down, and I'll explain how to compensate for that. For right now, we're just going to learn it this way. So when you think about this all together, just going over the whole graph that we have here, you would say that wherever the y value is 1, you're going to have a shared point. So that's going to happen at an x value of 0, and then an x value of 2 pi, and then 4 pi, 6 pi, 8 pi, so on and so forth. And then going this way, you'd have negative 2 pi, negative 4 pi, negative 6 pi, so on and so forth. So you could say at 2 pi n, where n is an integer, the y value would be 1, and you're going to have a shared point between your secant graph and your cosine graph. Then similarly, when you think about having a y value of negative 1, again, that's going to have a shared point. So something like, let's say, pi, negative 1. And if you add 2 pi to that, you'd have 3 pi, negative 1. If you subtracted away 2 pi, from this pi here, you'd have negative pi and then comma negative 1. And then here's your negative 3 pi comma negative 1. So this would be at pi plus 2 pi n, where n is any integer. So 5 pi comma negative 1 would be there, 7 pi comma negative 1 would be there, something like negative 5 pi comma negative 1 would be there, so on and so forth. The idea here is you want to think about that as being shared points, because when you see that there's a shared point, you're going to what we call interchange the hills and the valleys. So what I mean by that is, when you think about the graph of cosine, you know that you have a maximum point anywhere where the y value is 1 and a minimum point anywhere where the y value is negative 1, because the range of cosine is from negative 1 to positive 1 with both being included. So here you'd have a maximum point, and then again here, and then here. So when you think about it, this maximum point right here corresponds to what we call a local minimum point on the graph of the secant function. So this right here is a hill, and this right here is a valley. So the hills and the valleys are going to be interchanged. So this right here is a hill, this is a valley. Hill, valley. Then when we get down here, let me use a different color, you think about the fact that, okay, now when we look at our cosine graph, this is going to be a valley or a minimum, and then here this would be a local maximum or a hill. And then when you come here, it's the same thing. So this is a valley, this is a hill. Valley, and then this is a hill. You have a valley, and then this is a hill. So that's all you really need to memorize. The hills and the valleys will be interchanged. That's how pretty much every book says it, and that's how I remember it. Now the last thing, again, like we talked about a moment ago, is how to get these vertical asymptotes. So without shifting the graph up or down, you're going to think about where are the x-intercepts for the guide function, the cosine function. Again, that's going to happen at odd multiples of pi over 2. So at this negative 5 pi over 2, negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and then 5 pi over 2. So this would be a vertical asymptote here for your secant function. Again, you'd have one here, and then here, and then here, and then here, and then here. And again, this continues forever. So you would have 7 pi over 2, 9 pi over 2, so on and so forth. All right, let's just go through the characteristics of the secant curve. So the domain consists of all real numbers except odd multiples of pi over 2. Again, this is because at odd multiples of pi over 2, you're going to get a cosine value of 0, division by 0 is undefined. So f of x equals the secant of x is discontinuous at odd multiples of pi over 2. The graph contains vertical asymptotes at those values. There are no x-intercepts. You will only see those if you start shifting the graph up or down. And then the period is going to be 2 pi. So there are no minimum or maximum values. We saw that the range is from negative infinity going up to negative 1 and including negative 1. And then the union width you have from 1 and including 1 out to positive infinity. You will not see any y values between negative 1 and positive 1, again, because of the range of the cosine function, which is from negative 1 to positive 1, and the definition of the secant function, which is 1 over the cosine of x. Again, something we talked about earlier when we were describing the behavior of the graph. So the graph has no amplitude, again, because there are no minimum or maximum values, and the graph is symmetric with respect to the y-axis. So the secant of negative x is equal to the secant of x for all x in the domain. So we can say f of x equals the secant of x. That is an even function, just like cosine. All right, so real quick, we have a graphing procedure, and you can write this down if you want. It's something you can just memorize if you don't want to write it down. It's not a big deal. So graphing variations of the secant function. The first thing you want to do is replace the secant with cosine and sketch the graph using a dashed curve. So cosine is used as a guide. Then you want to sketch the vertical asymptotes. So this is the one that you really might have trouble with, this step right here. And the reason for that is that if you get a vertical shift involved, then you're not going to look for the x-intercepts of the cosine function or the guide function. It's going to be moved around, and I'll show you that when we get to an example. The way I remember it is these occur at 1/4 of the way and 3/4 of the way through the cosine cycle. Again, just going back to this, here is the cosine graph if you look at it over one cycle. So if we look at it over one cycle, it looks like that. So at the start of the cycle, your x value is 0. When you get 1/4 of the way through, your x value is pi over 2, so you have an x-intercept. When you get to the middle, your x value is pi. 3/4 of the way through, your x value is 3 pi over 2, so you have an x-intercept, and then you finish up at 2 pi for the x value. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. So just keep that in mind. When we look at these variations of this guy, we're going to use the same thought process. So 1/4 of the way through and 3/4 of the way through, that's where we're going to have our vertical asymptotes for the secant function. All right, then we have sketch the graph by drawing the U-shaped branches between consecutive vertical asymptotes. So you have that the hills and the valleys are interchanged. So all you're going to do is you're going to take those shared points, you're going to start there, you're going to make your U-shaped branches, and you're going to approach your asymptotes but not touch them. Then we have optional here, use the period to find additional cycles to the left or the right as needed. And again, if you're self-studying, I would just do one period and call it a day. Usually if you're given an assignment, your teacher will say, hey, I want you to sketch it from this place to this place, so just follow that. Okay, let's take a look at an example now. So we have f of x equals 1/2 secant of 2x plus 5 pi over 6, and then plus 1. So instead of just going straight into replacing secant with cosine, let's just get some information. So let's just go ahead and say that we have f of x is equal to 1/2, and then the secant of, I'm going to factor out the 2. It just makes it easier to find the phase shift. So pull that out, you're going to have x plus, how do I undo multiplication by 2? I would divide by 2 or multiply by 1/2. So this would be 5 pi over 6 times 1/2, which is 5 pi over 12. And so when we look at it now, finding the phase shift is very easy. You just want to say, inside the parentheses here, how do I undo what's being done to x? We have this plus 5 pi over 12. To undo that, you want to subtract away 5 pi over 12. So for the phase shift, you could say minus 5 pi over 12, or most people would just say left 5 pi over 12. Now, in terms of the vertical shift, that's very straightforward. So you have this plus 1 here. So the vertical shift, that's just going to be up 1. Now thinking about the period, so we'll need that. So what is the period for this guy? Again, the standard period is 2 pi when you're looking at either sine, cosine, secant, or cosecant. And we're just going to divide that by the number outside the parentheses here. If it's in unfactored form, it's the coefficient of x. So 2 pi over 2, which would be pi. And then for the quarter period, depending on the method you're going to use to find your points for the cosine function we're going to get in a minute, you would want to take this period, which is pi, and divide it by 4. So the quarter period is pi over 4. Now, let me put a little border here. I'm going to talk about the graphing transformations, and you can use this method if you want, or you can use a different method. It's really going to be up to you. So in terms of x, remember, this is the one that's really hard for students. That's why a lot of people just turn to the quarter period method, because this becomes a little bit challenging to remember. You need to undo what's being done to x. And so to undo something, you have to go in the reverse order. Think about writing a Word document or something like that. You hit Control Z. You're undoing the latest thing you did. You don't undo the first thing you did. So if you look at the order of operations here, again, you have parentheses here. And I know you could distribute that 2 in, but we're not doing that here. So from the order of operations, we know we would work inside the parentheses first and then do the multiplication second. So if I write this out, now I have to go in the reverse order. So this would be 1 and this would be 2. And each thing has to be undone. So how do I undo multiplication by 2? I would divide by 2 or multiply by 1/2. So you would multiply by 1/2. So that's giving me a horizontal shrink by a factor of 1/2. I know a lot of teachers will also say this as a horizontal compression by a factor of 2. Again, I don't want to get caught up on the terminology. A lot of people get confused by those two ways of saying the same thing. Just realize that you're having your x coordinate either divided by 2 or multiplied by 1/2. Then the second thing is you want to undo this plus 5 pi over 12. Well, we want to subtract 5 pi over 12. Again, we saw that earlier when we did the phase shift. That's going to shift me to the left 5 pi over 12. Then when you think about the transformations for y, these are the ones that are very straightforward. You have this 1/2 here that's multiplying this guy. So the first thing is you would just follow that. So multiply by 1/2. And the second thing is you're adding 1. So you're going to add 1. Again, this is straightforward. It follows the order of operations. You multiply before you add. So with this one, you're getting you could say vertical shrink by a factor of 1/2, or you could say vertical compression by a factor of 2. Again, I know that confuses people when you have two different ways to say the same thing, but just realize you're taking the y coordinate and you're either dividing it by 2 or you're multiplying it by 1/2, and then you're going to add 1. That's shifting me up by 1 unit. Okay, so coming to a new sheet here, I'm going to erase the secant and just put in cosine. So remember, we're going to graph this as a guide. So how do you graph this cosine function? Again, lots of ways to do it. You can use all graphing transformations. You can use no graphing transformations. It's really up to you. So I'm going to do both the quarter period method and all graphing transformations method. And then on the next ones, I'll just use the quarter period method because it's a little bit easier for students to understand. So when we think about using the quarter period method, you start off by thinking about your points for the basic cosine function. So y equals cosine of x. You have a point. You start off at the maximum, so 0, 1, and then you're going to go to your x-intercept. So this is pi over 2, 0, and then you're going to go to your minimum. So this would be at pi, -1. You go back to an x-intercept. So this is 3 pi over 2, 0, and then you're going to finish up at the maximum. So 2 pi, comma 1. So these are points you should have memorized at this point. And all we're going to do is think about, for the first x value here, you just use the phase shift. In other words, you have this 0 right here, and I'm going to think about what is the phase shift. So we know it's to the left by 5 pi over 12, or you could say I'm subtracting away 5 pi over 12. Again, I've got to undo what's being done to x there. So this x coordinate would be negative 5 pi over 12 right there. To get the additional x coordinates here, all you're going to do is you're going to take this value right here. Don't worry about these. This value right here, and you're going to keep adding quarter periods. So the quarter period, again, was pi over 4. You took your period, which is pi, divided by 4. Here I'm going to multiply this by 3 over 3, so we have a common denominator, so it's 3 pi over 12. So you're going to keep adding 3 pi over 12. Again, start here, negative 5 pi over 12 plus 3 pi over 12. That would give me negative 2 pi over 12. I know you could simplify that, but let's just hold off for a moment, so we have a common denominator. So negative 2 pi over 12 plus 3 pi over 12, that would give me pi over 12. Then pi over 12 plus 3 pi over 12, that's 4 pi over 12. Again, don't simplify it yet. 4 pi over 12 plus 3 pi over 12, that's 7 pi over 12. Now this right here, this 4 pi over 12, you could write that as pi over 3. So this is pi over 3. And then negative 2 pi over 12, you could write that as negative pi over 6. So negative pi over 6. Let me make this better here. Before we go on, I want to show you that you can get the same values here just using those graphing transformations that we talked about a moment ago. So coming back up here, let me grab this real quick and come down here and paste this in. And I'll just do the first 2 of them because this is a little bit time consuming. So for this one, you stick with these guys right here. So for 0, you multiply by half, you get 0. Then you subtract 5 pi over 12, you'd have negative 5 pi over 12. Then you would take pi over 2 and multiply by a half. So you do that first. And then you're going to subtract away 5 pi over 12. So this is very tedious because you have to get these common denominators. So this becomes pi over 4 minus 5 pi over 12. So we'll say this is, let's multiply this by 3 over 3. So 3 pi over 12 minus 5 pi over 12, which becomes negative 2 pi over 12, which is going to simplify to negative pi over 6. So you see you have negative pi over 6 there. Let's just do one more. I don't think we have to do all of them. You can do them all on your own. This is just to show you that you have different techniques to use. So we have multiply by a half. So let's start with pi. And we multiply by a half. And then we subtract away 5 pi over 12. So this becomes pi over 2 minus 5 pi over 12. Multiply this by 6 over 6. So you have 6 pi over 12 minus 5 pi over 12. So this would give you pi over 12. So pi over 12 there. So again, if you follow this, you get the same result as using the quarter period method. I know a lot of students do not like using graphing transformations for x because the procedure itself is hard to get. And then in this case, it would be a little bit more tedious than what we did with adding quarter periods. So we have our x coordinates. So that's the first thing. Let me put a comma, a comma, a comma, a comma, and a comma. And now we want to find the y coordinates. Now, this is one where you can use graphing transformations very easily. And that's because of the fact that when you plug in negative 5 pi over 12, so if I plug that in there, negative 5 pi over 12 plus 5 pi over 12, well, that's going to be 0. 2 times 0 is 0. So you would get the cosine of 0, which is 1. So notice that this right here, when I go through the process, I get this y coordinate right there. So I could have shortcutted that and not plugged in and just said, okay, well, it's going to be 1/2 times whatever this y value is, which is 1, and then plus 1. Again, if we go back, that's what we came up with here. Multiply by half and then add 1. That's all you're doing. When you look at this one here, again, if you plugged in, and I'll just do it for this one, negative pi over 6, if you plug that in there and you go through the steps, you're going to end up with this guy right here being 0. Because when you plug in a negative pi over 6 and you go through the steps, you're going to end up with the cosine of pi over 2. And let me just show you that real quick, just so that's crystal clear. If you did the cosine of, you have 2 times, let's plug in negative pi over 6, and then plus 5 pi over 12. Okay, so we just need this part right here. I'm going to multiply this by 2 over 2, so this would be negative 2 pi over 12. And what would that give me? Well, negative 2 pi over 12 plus 5 pi over 12, that's 3 pi over 12. And 3 pi over 12, you can say, is pi over 4. Well, 2 times pi over 4, that's going to be pi over 2. So the inside part here, this part right here, is going to be pi over 2, and the cosine of pi over 2 is 0. Well, notice that, again, the y-coordinate there is 0. So all I had to do was sit there and say that I know that the result of this will be 0. So I can just say, well, it's going to be 1/2 times 0 plus 1. And then if I was to plug in pi over 12, the result of this part right here would be negative 1. So 1/2 times -1 plus 1. Again, so on and so forth. These are just duplicates, so you don't have to do this. So I'm just going to say that this is 1/2 times 1, which is 1/2, plus, let's write 1 is 2 over 2, so this is 3/2. Then this one, anything times 0 is 0, so this is just 1. And then -1 times 1/2 is -1/2. And then plus, this will be 2 over 2, so this is 1/2. So this would be 3/2, 1, and 1/2. Let me erase this and write those in. So this is 3/2, 1, and 1/2. And again, for this one, it's going to be 1 again. And then for this one, it's going to be 3/2 again. When we think about graphing this guy, let me grab this real quick. I have given you a link for all of these guys that we're going to look at today on Desmos. So just click on that if you want something that has a little bit more detail or is easier for you to follow along with. So you can just pause the video and check these points out. But you see that at this point right here, again, at the beginning of the cycle, you have -5 pi over 12, 3/2. Then this right here is a quarter of the way through. You have -pi over 6, 1. So you want to focus on this one right here because this x value is where you're going to have your vertical asymptote. It's always going to be a quarter of the way through. And then you're going to have midway, you have pi over 12, 1/2. And then this one right here is 3/4 of the way through. Again, that's where you're going to take this x coordinate of pi over 3. You're going to have a vertical asymptote there. You're 3/4 of the way through. So pi over 3, 1. And then you're going to the end of the cycle, so 7 pi over 12, 3/2. What a lot of teachers will do is they will draw a horizontal line, which in this case would be y equals 1. They're showing you that the midline of this guy has been shifted up by 1 unit. So this right here would be y is equal to 1. So a lot of students will do that instead of remembering that it's at the quarter and 3/4 and just say, okay, well, anywhere where there's a point that's on that line, well, this has been shifted up like that. So I'll look at the x coordinate. In this case, it's -pi over 6. It's covered up a little bit. In this case, it's pi over 3. And that's where I'm going to have the vertical asymptotes drawn. So go to the next graph. That's what we have. So here's your x equals -pi over 6. Here's your x equals pi over 3. That's all you're focused on. This is a quarter of the way through and 3/4 of the way through. That's how you want to draw this in terms of getting the vertical asymptotes for the secant function. Now, once you have that, you're ready to put everything together. So let me just highlight this again. So we have this vertical asymptote and this vertical asymptote. So this is extended to the left and to the right a little bit. But again, if you're doing this on your own, you're going to have this point right here that we found, this point right here that we found, and this point right here that we found. Again, this point right here and this point right here, that's not really relevant anymore because we use it to make the vertical asymptotes, so we don't need that. The idea is that, again, when you see a hill here, it becomes a valley here. So that means that this right here would be drawn to where it approaches that vertical asymptote. And then this right here would be drawn to where it approaches the vertical asymptote. Same thing for this part right here. And again, the way you know that this is going down like that, this right here is going to be a valley, so this right here becomes a hill. This minimum here becomes a local maximum here. This maximum here on the cosine guide is going to become a local minimum here. Then when we look at this part right here, so again, this is a hill, so this would be a valley, so this maximum here on the cosine guide is going to be a local minimum on the secant graph. So this guy right here would be drawn to where it approaches the vertical asymptote and doesn't touch it. All right, let's take a look at another example with secant. So here we have f of x equals the secant of x over 3 minus 2 pi over 3 plus 1. So again, let me just factor this guy so we can get the phase shift more easily. Let me make that a little bit better. So this is the secant of, I'm going to pull out a 1/3, and this one's very straightforward. Let me slide this down so I have room. So inside you'd have x minus 2 pi, close that down, close this down, then plus 1. Okay, so looking at this, just getting some information, if you want the phase shift, which we're going to use with the quarter period method, you have to undo what's being done to x. So you have this minus 2 pi here. So I'm going to add 2 pi to undo that. So that means I'm going to the right. So I'm going to the right by 2 pi. Then for the vertical shift, again, you have this plus 1 here. So that means I'm going up 1. For the period, again, you're going to take the standard period, which is 2 pi, and you're going to divide by this number outside the parentheses in factored form, or if it's not in factored form, you had that x over 3, so the coefficient of x is 1/3. So it's just 2 pi divided by 1/3, which is 2 pi times 3, which is 6 pi. So your period here is going to be 6 pi, and then the quarter period, that's going to be 6 pi over 4. Let me slide down a little bit. So 6 pi over 4, 6 divided by 2 is 3. And then 4 divided by 2 is 2. So it's 3 pi over 2. Okay, so if you want to do this using graphing transformations, again, typically we always do that for y, but for x, it just depends on the student. I'll just give you the information. If you want to do it that way, that's up to you. So let me put out x and y here. So for x, again, you have to undo what's being done to it. And to do that, you go in the reverse order. So as we talked about in the first problem, this is done first and this is done second because you're reversing the order of operations. You go inside the parentheses first, so now this would be second, and you multiply second, so now this would be first. And you have to undo what's being done. So multiplying by a third, to undo that, you need to multiply by 3. So multiply by 3. And then to undo this subtraction of 2 pi, you need to add 2 pi. So add 2 pi. And so what's happening is this multiplying by 3, that's giving you a horizontal stretch by a factor of 3. And then adding 2 pi, that's going to shift me to the right by 2 pi. And then for y, again, that's very straightforward. You don't have anything outside here. You can just put a 1 if you want. So really, I put 1 and 2, but you just need one thing here. So you wouldn't even consider that because multiplying by 1 is not going to change anything. So really, all you have to do here is just add 1, and so that just shifts me up by 1 unit. So again, if you want to do it this way, it's up to you. I'm going to use the quarter period method because most students find that easier. So let me go ahead and grab this real quick, and I'm just going to erase this and just write in a cosine. Okay, so going back to the basic points we had, so we're going to say that we have 0, 1, again, starting at the maximum. Then you have pi over 2, 0, that's your x-intercept. Then you have pi, -1, so down to the minimum. Then you have 3 pi over 2, 0, so that's your x-intercept. Let me slide down a little bit. And then you'd have 2 pi, 1, so you're at the maximum for the end of the cycle. So we're going to, again, you can use the quarter period method or you can use the graphing transformations that we wrote on the other page. We're going to find the x-coordinates first. So again, you would start with a shift because this guy right here is 0. So you're just going to add 2 pi because we're shifting 2 pi to the right. So this guy is going to occur at 2 pi now. And then from that point on, you're just going to add quarter periods. So the period was 6 pi and the quarter period was 3 pi over 2. So if I add that to 2 pi, what that's going to give me, let me multiply this by 2 over 2. So you could say this is 4 pi over 2. So this would give me 7 pi over 2. So this is 7 pi over 2. And then from this point on, you're just going to keep adding 3 pi over 2. So 7 pi over 2 plus 3 pi over 2, that's 10 pi over 2. Again, you could simplify that, but we'll do it in a moment. 10 pi over 2 plus 3 pi over 2, that's 13 pi over 2. And then 13 pi over 2 plus 3 pi over 2, that's 16 pi over 2. So this right here would be 5 pi if you simplified. And then this right here would be 8 pi if you simplified. Okay, so now that we have the x-coordinates, again, for the y-coordinate, you can just use graphing transformations. You could plug in if you want, but again, it's the same thing. So what I would do is I would just say that whatever the y-coordinate is here, I'm just going to add 1 because we're shifting up by 1 unit. So 1 plus 1 is 2. 0 plus 1 is 1. -1 plus 1 is 0. And again, for this one and this one, you can just copy. So for 0, it goes to 1, and then for 1, it goes to 2. And let me paste this in. Once again, I'll just mention this. I have a link for you on Desmos if you want to follow along more closely. Maybe you're having trouble because of the scale of the graph or you're using a smaller device or something like that. But you see the beginning of the cycle, we have this 2 pi, 2, then we have 7 pi over 2, 1, then we have 5 pi, 0, you have 13 pi over 2, 1, and then 8 pi, 2. The common mistake that students make is they're not paying attention and they say, okay, I have an x-intercept here, so they draw a vertical asymptote. That's wrong. You want to look at what happens at the quarter, so at the quarter, and 3/4, okay, because this guy has been shifted up by 1 unit. Again, a lot of teachers will take and draw that new midline. So this is y equals 1. Normally it's y equals 0 or the x-axis, but because of the plus 1, it's shifted up by 1 unit. So whenever you have a point that's on that line, you're going to take the x value there, and you're going to say that's where my vertical asymptote is going to be for the secant function. So x equals 7 pi over 2 would be a vertical asymptote. X equals 13 pi over 2 would be a vertical asymptote, so on and so forth. Again, if you want to continue this to the left or the right, that's going to be up to you. Again, you can keep adding quarter periods to your x values to keep going to the right. Remember, the y values are going to cycle. So for the beginning, it's 2. Then for the quarter, it's 1. Halfway, it's 0. Then for the 3/4, it's going to be 1. And then finish up at 2. All right, so continuing, again, at x equals 7 pi over 2, you can have a vertical asymptote. And then at x equals 13 pi over 2, you can have a vertical asymptote. Okay, so coming to the graph, let me just highlight what we just did. So this is your x equals 7 pi over 2. This is your x equals 13 pi over 2. So those are the 2 vertical asymptotes we found for the secant function. And again, all you want to do is you want to take that point, and let's just say it's about right there, and you're going to sketch this to where it approaches the vertical asymptote. when you look at this right here for the cosine, this is a hill, so here it's going to be a valley. So this maximum becomes the local minimum here. And then again, similarly, let's say we make a point about right there, and we would say that you could go this guy approaching the vertical asymptote, and then this way you would approach the vertical asymptote. So just like that. Again, it does not have to be perfect. Just get it as good as you can. Again, this valley right here on the cosine graph becomes a local maximum on the secant graph. Let's say you have this point about right there that you found. So this guy right here would be drawn to approach the vertical asymptote, but not touch it. Again, if you want to extend this to the right or to the left, you can click the link on Desmos and just practice that way. But generally just drawing one cycle of this guy, particularly if you're self-studying, that's good enough. All right, now let's change things up and look at the cosecant function. So with this one, you're going to see that a lot of things we learned with the secant function is just going to carry over. So let's do y equals the cosecant of x. And again, I'm going to do this over one period. Now, negative pi and pi will not be included here because that's going to give you undefined. So let's say that x is strictly greater than negative pi and strictly less than pi. So let's think about this using the unit circle. Let me come back up here for a moment. So remember that the cosecant of x, by definition, is 1 over the sine of x. So a moment ago, I said that it would be undefined at negative pi and pi, but just thinking about where the sine value is 0, so that's right here at 0, right here at pi, so just using the standard unit circle. But again, this is going to repeat every pi. So you have 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, so on and so forth. Or if you wanted to rotate clockwise, you could say, and let me just show you this real quick, if you rotated like this, this would be negative pi. So that is negative pi, that is coterminal with pi. So it's the same sine value. So you could do negative pi, negative 2 pi, negative 3 pi, negative 4 pi, stuff like that. You're still going to get an undefined value for cosecant because the sine value is 0. So going back, you will see that anywhere where the sine value is 0, you're going to get these vertical asymptotes. So again, at negative pi, you're going to get 1. You get 1 at 0, but you typically do not put a dashed line right there because this is the y-axis. So you can put 1 in if you want. Just know that that is a vertical asymptote. So it would be x equals 0, or again, the y-axis. And then here you have pi. But if you keep going, you'd have 2 pi, 3 pi, 4 pi. If you kept going this way, you'd have negative 2 pi, negative 3 pi, negative 4 pi, so on and so forth. So you can basically say this is going to happen at pi n, where n is any integer. When you look at this point right here, so this point right here, you have a y value of 1. So this will be a shared point for cosecant and also for sine. And then here, you have a y value of negative 1. That'll be a shared point for cosecant and for sine. And I'll show you that when we get to the combined graph. So just remember this point right here. This is going to be pi over 2 comma 1. And then this point right here, this is going to be negative pi over 2. Remember, that's coterminal with 3 pi over 2, and then comma negative 1. So again, just thinking about the behavior of this guy, as you go from pi over 2 for that x value, where the sine value is 1, to an x value of pi, where the sine value is 0, well, again, because the cosecant of x, let me write this out, it's because the cosecant of x is equal to 1 over the sine of x, well, the value here, as you go this way and you get closer to an x value of pi, it's getting closer and closer to 0, but it's never going to touch it. So 1 over something that's really, really close to 0, again, this is going to blow up, and we say this increases without bound, or it's approaching positive infinity. Then similarly over here, if you follow this part right here, you're going to decrease without bound or approach negative infinity. So just like we saw with the secant function, same process is happening. It's just happening at different places on the graph. Now, we can go through a few basic points. This is just something you can read through for reference. So if the x value is 0, again, y is undefined. This is also going to happen at plus or minus pi. You would get undefined. Again, this is pi n, where n is an integer, because you have a sine value of 0. Then when you think about something like pi over 6, you get 2. Again, just to show you that one, just so this is crystal clear, if you look at this right here, this is pi over 6. Well, the sine value is a half. So the cosecant of pi over 6 is 1 over the sine of pi over 6, which equals 1 over 1/2, which again is 2. If you looked at negative pi over 6, I'm rotating clockwise. So we saw that earlier, and so this is coterminal with 11 pi over 6. But the thing is, cosecant and sine, they are negative in quadrant 4. So that means I'm going to get the opposite of this. So I would want negative 2. So the cosecant of negative pi over 6 is equal to 1 over the sine of negative pi over 6, which is equal to 1 over negative 1/2. Again, you can take that y coordinate right there. And so this is equal to negative 2. So that's why these guys are opposites. So coming back down, let's think about you have pi over 4, that's square root of 2. Then negative pi over 4 would be negative square root of 2. Again, they're opposites. Pi over 3, you have 2 times square root of 3 over 3. Negative pi over 3, you have negative 2 times square root of 3 over 3. Then pi over 2, you get 1. Negative pi over 2, you get negative 1. Then you have 2 pi over 3, you get 2 times square root of 3 over 3. Negative 2 pi over 3, you get negative 2 times square root of 3 over 3. 3 pi over 4, you get square root of 2. Negative 3 pi over 4, you get negative square root of 2. And then 5 pi over 6, you get 2. And negative 5 pi over 6, you get negative 2. So just like we saw with secant and cosine, we're going to use the sine function as a guide when we graph cosecant. Again, where there's a y value of 1, you're going to have a shared point. Where there's a y value of negative 1, you're going to have a shared point. So you're going to use those shared points. Again, when you have a hill here, you're getting a valley here. So this maximum here, again, the range for sine is the same as the range for cosine. It's from negative 1 to positive 1 with both being included. So whenever you have a y value of 1, you're at a maximum on your sine graph. So a maximum here gives me a local minimum here. Again, there is no minimum or maximum for the cosecant function or the secant function, but you do have those local minimums and local maximums. Some books call that the relative minimum and the relative maximum if you're used to that terminology. But this hill right here becomes a valley here, or you could say this maximum here becomes a local minimum here. Then this valley right here becomes a hill here. So in other words, this minimum here becomes a local maximum here, and so on and so forth. Then again, the other thing I would call your attention to is that in this form, because there's no vertical shift, when you look at where you have the x-intercepts on your sine graph, that's where you're going to have your vertical asymptotes for the cosecant graph. So something like pi, you would also have 0. Again, we typically do not draw that in for the y-axis. If you want to, it's not wrong. But you would have 0, pi, 2 pi, 3 pi, again, going over here, negative pi, negative 2 pi, negative 3 pi, so on and so forth. So just like we saw with the secant function, the range here is going to be from negative infinity to negative 1, where that's included, and the union with 1 going out to positive infinity. So you don't have any y values between negative 1 and positive 1. All right, let's spend a little bit of time looking at the characteristics of the cosecant curve. So we have here that the domain consists of all real numbers except pi n, where n is any integer. Again, that's because the sine value would be 0 there, and so your cosecant function would be undefined. We have f of x equals cosecant of x is discontinuous. Again, if there's pi n, where n is any integer, and the graph contains vertical asymptotes at those values. There are no x-intercepts. You're only going to get those when you start shifting the graph up or down. But on the standard y equals cosecant of x, there are no x-intercepts. The period is 2 pi. There are no minimum or maximum values. Of course, we have those local minimums and local maximums that we use to sketch the graph. The range is from negative infinity to negative 1, with this guy being included, and the union with, you have 1 to positive infinity, again, where 1 is included, but you don't have any y values between negative 1 and positive 1. So keep that in mind. The graph has no amplitude because, again, there are no minimum or maximum values. You're just going to see amplitude when you work with cosine and sine. Now, the graph is symmetric with respect to the origin. So the cosecant of negative x is equal to the negative of the cosecant of x for all x in the domain. So f of x equals the cosecant of x is an odd function. So just like the sine function. All right, so now let's talk about graphing variations of the cosecant function. So this is pretty much the same thing as we saw with the secant function directions. So we're going to replace cosecant with sine and sketch the graph using a dashed curve. So that's your guide function. Sine is used as a guide. Sketch the vertical asymptotes. Again, when you think about this, because you have vertical shifts, you cannot just say that the vertical asymptotes will occur wherever the x-intercepts are on the sine graph that you're using as a guide. That will only work if you don't have any vertical shifts. So what I always teach people is they occur at the beginning, middle, and end of the sine cycle. Because remember, on your normal sine graph, you have, let me just come back to this for a moment. So your cycle is going to go from right here to right here. So from 0 to 2 pi. You're going to start out at an x-intercept. You're coming up to the maximum, and then you're coming back down to an x-intercept. So right there. Let me do that in a different color. And actually, let me mark this one, and this one, and this one in a different color, and go back to this one. So let me come down. So you're going down to the minimum, and then you're coming back up to the end of the cycle, which is an x-intercept. So the beginning, the middle, and the end. If you remember that this midline is y equals 0, so you're on the x-axis. If you had something like a vertical shift up by 1, well, then that midline is going to be y equals 1. If it was, let's say, a shift down by 4, well, now it would be y equals negative 4. So a lot of people will draw that midline in. You can do that. But what I always do is just say, okay, what point am I going to have that's first, third, and fifth? So at the beginning, the middle, and the end, that's where I'm going to take those x values and draw my vertical asymptotes for the cosecant function I'm working with. All right, then I have sketched the graph by drawing the U-shaped branches between consecutive vertical asymptotes. So these guys are going to approach the vertical asymptotes, but not touch them. And we have here the hills and valleys are interchanged. And then optional, I have used the period to find additional cycles to the left or right as needed. If you're self-studying, I recommend just doing one period. You can, of course, just look on Desmos and see it to the left or right as much as you want. But if you're getting this from a teacher as an assignment, they'll generally tell you, well, I want you to sketch it over this interval. So just follow that. All right, let's take a look at an example. So we have f of x equals 1/2 cosecant of x plus pi over 3 and then plus 2. So normally I would factor this so I can get the phase shift. But here, the coefficient on x is 1, so you don't really need to factor anything. You can immediately just get the phase shift and say that we're going to go left by pi over 3. Again, you've got to undo what's being done to x. You have plus pi over 3, so that means you need to do minus pi over 3. So that tells me I'm going left pi over 3. And then in terms of your vertical shift, you're going to have plus 2 here. So that means I'm going up 2. So if you wanted to graph a horizontal line through the middle of that guy, when you're graphing the sine function as a guide, you would sketch y equals 2 for that. Because normally it's y equals 0, and this has shifted me up by 2 units. So for the period, it's just the standard 2 pi. So you take 2 pi and you divide by the coefficient of x. And so in this case, that's 1, so it's just 2 pi. And then the quarter period, if you're using that method, well, it's just going to be 2 pi over 4, which would be pi over 2. So if you want to use graphing transformations, then let's just put down for x here, you only have one thing you'd have to do. Again, you're just shifting to the left by pi over 3. So you would just subtract away pi over 3. And that's from each x value from your standard points for the, and we're going to work with the sine function in a moment when I swap this out. So for the sine function. And then in terms of the y, you have two things you need to do. Let me put a little border here. The first thing is you multiply by 1/2. You multiply by 1/2. And the second thing is you add 2. So we're going to use this. If you want to use this, that's up to you. In this case, I think it's probably equal time to using the quarter period method, but a lot of people do not like using graphing transformations for x for whatever reason. So thinking about this, this gives me a shift to the left by pi over 3. This right here gives me a vertical compression by a factor of 2, or again, you might say a vertical shrink by a factor of 1/2. Again, I will not get into a debate about that. Just understand that you're either dividing by 2 or you're multiplying by 1/2 for each y coordinate. And then you're going to add 2, that's shifting me up by 2 units. And come down here and paste this in so I have some room. So I'm just going to rewrite f of x equals 1/2 sine of x plus pi over 3, and then plus 2. Okay, let me get rid of this. Move this up. And we just need to get our points. So just start with your standard points for sine. So you have 0, 0, you have pi over 2, 1, then you have pi, 0, you have 3 pi over 2, -1, and then you're going to finish up at 2 pi, 0. So all you have to do is start things off with your phase shift. So that is going to be minus pi over 3. So you take 0, subtract away pi over 3. So that gives me negative pi over 3. Once I've done that, I'm just going to add quarter periods. That's all I need to do. So again, if you're using this method, you're not going to touch any of these x values. You're only going to do that if you're using the graphing transformations method. And I know that gets confusing, but essentially you're just saying, okay, well, the quarter period here is going to be pi over 2. I need a common denominator. Let me multiply this by 2 over 2. Let me multiply this by 3 over 3. So that would give me 3 pi over 6. So 3 pi over 6. And this would be negative 2 pi, so negative 2 pi over 6. You can erase this now. So I'm going to add 3 pi over 6. So that gives me pi over 6. So this is pi over 6. And again, you're just going to keep doing this. So you're just going to keep adding 3 pi over 6. Pi over 6 plus 3 pi over 6, that is 4 pi over 6. Don't simplify yet. 4 pi over 6 plus 3 pi over 6, 7 pi over 6. 7 pi over 6 plus 3 pi over 6, 10 pi over 6. Okay, so now you can simplify. You just want to make sure you're not simplifying, and then you got to get a common denominator again. So 4 pi over 6, 4 divided by 2 is 2, and 6 divided by 2 is 3, so it's 2 pi over 3. And then 10 pi over 6, 10 divided by 2 is 5, and 6 divided by 2 is 3, so that's 5 pi over 3. The other way you could have done this, we only have one thing we're doing to x. We need to subtract away pi over 3. So if you're using that method, you're working off of these values only. So 0 minus pi over 3, negative pi over 3. Pi over 2, let me show you this real quick. So pi over 2 minus pi over 3. Let me make that better here. That's going to give you pi over 6. So if I multiply this by 3 over 3, multiply this by 2 over 2, I would have 3 pi minus 2 pi. and this is over 6, and of course that is pi over 6, same thing as I got right there. And you can keep doing this if you want. You could do pi minus pi over 3. Let me just do one more of them, just so this is crystal clear how you can use the different methods. So let's write 3 pi over 3 minus pi over 3, and of course that gives you 2 pi over 3. So you're getting the same thing. So it's the same result either way. You just have to be completely clear on which method you're using and what steps work with each method. I don't want anybody to get confused. With that being said, let's go through and get our y values. Again, you can always plug in, but you know that if you plug in negative pi over 3 right here, this part right here is going to become this right here. Again, negative pi over 3 plus pi over 3 is 0. The sine of 0 is 0. So this becomes this right here. So the shortcut is, again, just to use graphing transformations, you're just going to say multiply by 1/2 times whatever this is, so that's 0, then plus 2. So then this would be 1/2 times this guy right here, this 1, and then plus 2. So on and so forth. So this right here would be 1/2 times your 0 again, and then plus your 2. And of course, this is a duplicate of this, so you don't have to do this one. We can just erase this one. You could do this one. So 1/2 times negative 1, and then plus 2. So this would be 2. We know that 1/2 times 0 is 0, and you add 2, so you get 2. So this one's 2, and of course, this one's 2, and of course, this one's 2. For this one, 1/2 times 1 is 1/2, and then plus 2, you could say this is 1/2 plus 4 over 2, so this is 5 over 2. So 5/2 is what you're looking for there. Okay, here, this would be 1/2 times negative 1, that's negative 1/2, and then plus 2, so let's say plus 4 over 2, and that would be 3/2, so that would be for that one. So not too bad overall. Again, getting the y values is always much easier. Let me go ahead and grab this real quick. And let me come down here and paste this in. And really, I don't need these. I just need these. So let me move this over so you can see everything. Again, I gave you a link for Desmos if you want to click on that. But essentially, when we graph this sine function as a guide, you have this negative pi over 3 comma 2. You have this pi over 6 comma 5/2. You have 2 pi over 3 comma 2. You have 7 pi over 6 comma 3/2. And then you have 5 pi over 3 comma 2. Remember, when you think about this, at the beginning, the middle, and the end, again, that's where you have your x-intercepts on that basic sine function. This guy right here has been shifted up by 2 units. Again, this is what a lot of teachers do to make this crystal clear. So this is y equals 2. Again, it was y equals 0, but you have this plus 2 here that shifted everything up. So anywhere where you're hitting that line, y equals 2, where your y coordinate is 2, so that means that the x value there, that's going to be a place where the cosecant function is undefined, so you'd have a vertical asymptote. In other words, if I plugged in a negative pi over 3, negative pi over 3 plus pi over 3, that's 0. The sine of 0 is 0. But again, if you had the cosecant of 0, you would get undefined because the sine value is 0. Same thing would happen with 2 pi over 3, and this is 5 pi over 3. Hard to see it because it's circled. Let me recircle it here in a smaller way. So the idea is you'd have a vertical asymptote here at x equals negative pi over 3, and then here at x equals 2 pi over 3, and then here at x equals 5 pi over 3. So just showing this to you. So we draw these in as x equals negative pi over 3, and then you can have x equals 2 pi over 3, and then x equals 5 pi over 3. All right, so let's put everything together. Again, here's your vertical asymptote, x equals negative pi over 3. Here's your x equals 2 pi over 3, so another vertical asymptote. And then here's your x equals 5 pi over 3. Of course, you can use your period to get additional vertical asymptotes going to the right or to the left, just depending on how far you want to extend this. But what I'm going to do right now is just concentrate on what we worked on. So we know that we had a point that was, let's just say, about right there, and then one that was about, let's just say, right there. So again, you're going to interchange your hills and your valleys. So this right here is going to be a hill for the sine function, the guide function. So that would mean that it's going to be a valley here. In other words, this maximum point on your sine function here becomes a local minimum on the cosecant function here. And then with this guy, you have a valley on the sine function, so that becomes a hill on the cosecant function. Or another way to say that is you have a minimum on your sine function, and then that's going to turn into a local maximum on your cosecant function. So what we're going to do is draw this to where it approaches the vertical asymptote, but doesn't touch it. So there's that one, and then I'll do that over here as well. And then I'll come down here, same thing. So approaches the vertical asymptote, but doesn't touch it. And then let me do this part right here. So again, that would be good enough for me if I'm self-studying. You've done one period. So if you want to continue this to the left or the right, again, you have that link on Desmos. You can calculate all the things you need, and then you could just use that link to check it. All right, let's take a look at another example here with cosecant. So f of x equals 2, cosecant of x over 2 minus 5 pi over 6, and then minus 1. So again, I'm going to factor this just to get things started. So f of x equals 2 cosecant of, pull out a 1/2. And so inside you'd have x minus, if I'm pulling out a 1/2, how do I undo multiplication by half? I need to multiply by 2. So this one, you might need to write it out. So 5 pi over 6 times 2. And so this would cancel with this and give me a 3 down there. So this is 5 pi over 3. And I know this gets a little bit tricky when you're factoring like that, but you can always check it. A half times x is 1/2 x, or x over 2. Then minus and minus, 1/2 times 5 pi over 3, that is 5 pi over 6. So that checks. So then we have minus 1. So at this point, we can just get the phase shift right away. That's why I factor. So for the phase shift, you're going to get, again, how do I undo this minus 5 pi over 3? I need to add 5 pi over 3. So I'm going to the right, 5 pi over 3. This part right here is a vertical shift. I'm going down by 1 unit. So vertical shift. So it's down 1 unit. Then for the period, so for the period, you look at this 1/2 here. That again is the coefficient of x in unfactored form. In factored form, it's outside the parentheses. But essentially, you take your 2 pi, which is your standard period, and you divide by 1/2. Well, if I divide by 1/2, it's like multiplying by 2. So this gives me 4 pi for the period. If you want the quarter period, because you're using that method, so the quarter period, well, you just take 4 pi, you divide by 4, you get pi. That's all it is. If you want to do graphing transformations, again, it was more simple on the last one. This one, you have 2 things that are happening on the inside. So again, you've got to undo things. And to undo something, you have to go in the reverse order. Essentially, if you look at this, I'm going to go inside of the parentheses first if I'm using the order of operations. I know you can distribute this, but just the way it is, I would go inside of this first, and then I would multiply second. So I've got to undo this in the reverse order. So now this is 1, and this is 2. And I'm undoing things. So for x, how do I undo multiplication by 1/2 or division by 2? Well, I'm going to multiply by 2. So I'm going to multiply by 2. So in other words, I have a horizontal stretch by a factor of 2. Then this guy right here, I need to undo the subtraction of 5 pi over 3. Well, that means I need to add 5 pi over 3. So I'm going to add 5 pi over 3, and that shifted me to the right by 5 pi over 3. Then, again, for the y, this is always much easier and very straightforward. You just follow the order of operations. So you have that 2 that's multiplying this. So we're going to multiply by 2. And that's going to give me a vertical stretch by a factor of 2. And then the second thing is you have this minus 1. So we're going to subtract 1. And then that is just going to shift me down by 1 unit. So if you want to use this, that's fine. You just take those original points for your sine graph, and then you take the x coordinates. You're going to take each one, multiply by 2, and then add 5 pi over 3. That's going to be slower in this case because of getting common denominators. It's going to be faster to use the quarter period method. So I'm just going to stick with that. Maybe I'll show you 1 or 2 points with this just for clarity. So let me go ahead and grab this, and let's paste this in. And of course, what we're going to do is get rid of that cosecant, and we're going to sketch the graph of the guide function. So we're going to put in a sine and make the n better there. All right, so once we look at this, again, you think about your basic points for the sine graph. So you have 0, 0. You have pi over 2, comma, positive 1. You have pi, comma, 0. You have 3 pi over 2, comma, negative 1. And then you're going to have 2 pi, comma, 0. All right, so let me start out by doing the quarter period method. And then once we've done that, I'll do a few points using the graphing transformations. So the quarter period here is going to be pi. Now your phase shift is plus 5 pi over 3. So what you'd want to do is write this with a common denominator. And you could say this is 3 pi over 3. That 3 could be a lot better. And so the first thing here is going to be, I'm just going to shift to the right by 5 pi over 3. So I'm going to say instead of 0, now I have 5 pi over 3. And then to get the additional guys here, you're just going to keep adding quarter periods. So don't worry about these x values here. You're done with that. You just want to add this guy right here to this guy right here, and then just keep going. So 5 pi over 3 plus 3 pi over 3, that is 8 pi over 3. Then 8 pi over 3 plus 3 pi over 3, that is 11 pi over 3. Then 11 pi over 3 plus 3 pi over 3, that is 14 pi over 3. That one could be better. And then 14 pi over 3 plus 3 pi over 3, that is 17 pi over 3. So it's pretty quick in a lot of cases once you get a common denominator. All right, so the next thing is, if you wanted to try this with graphing transformations, again, we were told to multiply by 2 and then add 5 pi over 3. So with this one, you are working with these x values. This one you can just skip because you're multiplying by 0 first, and then you're adding 5 pi over 3. So of course you're going to get 5 pi over 3. But for this one, let's just try it. So pi over 2, you're going to multiply by 2 first and then add 5 pi over 3. So let's say if we do get 8 pi over 3. So this right here would cancel. And what do you get? You get 3 pi over 3 plus 5 pi over 3. Let me make this 5 better. And of course, you do get 8 pi over 3. So let me get rid of this. And you can see that works. If you want to do the rest of them that way, that's up to you. All right, so for the other guy, we need our y coordinate. And for that, we're going to use graphing transformations. Again, if you plugged in 5 pi over 3, this part right here would turn into 0. So to shortcut that, all you have to do is say, well, I have this guy 2 right here, times whatever this would be. In this case, it would be 0. And then you have minus 1. And then for this one, it would be 2 times this would be 1, and then minus 1. And this is going to be a repeat, so we just have to do this one. So you would have 2 times, again, this right here would end up being negative 1, and then minus 1. So 2 times 0 is 0, and then you have minus 1, which is just negative 1. So minus 1, 2 times 1 is 2, minus 1 is 1. So you can put that there. And then this one's just going to be a copy, so it's negative 1. And then 2 times negative 1 is negative 2. Negative 2 minus 1 is negative 3. So this is negative 3. And then this one you can copy, it's negative 1. Okay, let me paste this in here real quick. I'm just going to erase this. And so at the beginning of the cycle, you have 5 pi over 3 comma negative 1. Then at a quarter of the way through, you have 8 pi over 3 comma 1. Then at the middle part, you have 11 pi over 3 comma negative 1. Then 3/4 of the way, you have 14 pi over 3 comma negative 3. And then finishing up the cycle, at the end, we have 17 pi over 3 comma negative 1. So you can get rid of these. Again, where you're looking for where to put your vertical asymptotes, again, at the beginning, the middle, and the end. So just remember that. Beginning, middle, and end. The horizontal line that passes through the middle of this guy is going to be at y equals negative 1 now because you've shifted down by 1 unit. You have that minus 1 there. So this is y equals negative 1 there. A lot of teachers do this to say, hey, if you have a point that hits that midline there, well, you want to take the x value there, and you're going to use that to create a vertical asymptote for your cosecant function. That's all you have to remember. So we'll have one at 5 pi over 3, 11 pi over 3, and then 17 pi over 3. So there's your vertical asymptotes. Again, here's one at 5 pi over 3, here's one at 11 pi over 3, and then here's one at 17 pi over 3. So putting everything together, let's do again the x equals 5 pi over 3, a vertical asymptote. And then the other one that we saw, x equals 11 pi over 3. And then the last one that we found was x equals 17 pi over 3. So we've got those. Again, you can always get ones to the left or to the right, going as far out as you want. And then in this cycle here, we know that we found a point. Let's just say it's about right there. And we had a point. Again, let's just say that one was about right there. So the idea here is that this hill on your sine graph, the guide graph, is going to become a valley on the cosecant graph. Or again, you can always say that this maximum here on the sine graph will turn into a local minimum here on the cosecant graph. Then when we get to this point here, again, this is a valley on the sine graph, so it becomes a hill on the cosecant graph. Or again, another way to say that is that this minimum here on your sine graph is going to become a local maximum on the cosecant graph. So once you have that down, you're just going to sketch this guy again to where this is going to approach the vertical asymptote, but not touch it. And again, just approach the vertical asymptote and not touch it. And then this guy will do the same thing here. So approach the vertical asymptote and not touch it. And then approach the vertical asymptote and not touch it. Once again, I gave you a link on Desmos. If you want to do some additional practice, you can go to the left or to the right by as much as you want and just use Desmos to check your work. In this lesson, we want to talk about fundamental identities in trigonometry. So at this point, we've already talked about the reciprocal identities. We've talked about the quotient identities and the Pythagorean identities. If you forgot all that stuff because it's been a while since we covered it, it's okay. I'm going to pull up a quick little cheat sheet in a moment. Before we get into what we can do with the fundamental identities, I've got to give you one other piece of this puzzle, okay? And that's going to be the negative angle identities, which some books call the even-odd identities, okay? So it just depends on your textbook which name you're going to use. Now, when we look at this little graph here, we're going to consider two angles. One is going to be this angle theta, okay? So here's your initial side, here's your terminal side. And you can see this point here on the terminal side is just marked with x comma y, just generically. If I had a negative theta, so the negative of this guy, so now we're moving clockwise. Well, this point here on the terminal side, notice how it's x comma negative y, right? So this is the y up here, and this y down here is the negative of that. Notice how the x value is the same, okay? So we're going to use that to build this little relationship here. We're going to first start with sine of theta, okay? So sine of this guy right here, this would be equal to what? It's always y over r. But when I think about sine of negative theta now, how do things change? Remember, now I'm dealing with the negative of y, okay? So the negative of y over, it's still going to be r, okay? So what I can see here is that these guys are going to be negatives of each other. This guy is y over r, and this guy is going to be the negative of y over r. So I can use that to build a little relationship that's always going to be true, and I can just say that the sine of a negative theta is always going to be equal to the negative of the sine of theta, okay? So this is your first negative angle identity. Now, you might notice that this looks very familiar from earlier when we worked with functions and we talked about even and odd functions, right? This property here is from odd functions, right? So this is an odd function. If you had something like f of negative x, and you said this was equal to the negative of f of x, remember, this is an odd function. That's how you check for it. So let's erase this and think about cosine now. So with the cosine of, let's say, theta, okay, what is it? It's x over r. So it's x over r. But now when I look at the cosine of negative theta, okay, it's the same x, right? The x is the same. You have x comma y, you have x comma negative y. So x is not changing, okay? So we can say that the cosine of theta is equal to the cosine of negative theta. Remember, this is a property of even functions. So we'll say that the cosine of theta is equal to cosine of negative theta, okay? All right, so lastly, I'm going to take the relationships here, and I'm going to build something with tangent, okay? So I know that the tangent of theta is equal to the sine of theta over the cosine of theta. Now, let's think about this. If I had a negative theta, then all of these would just be negative theta, right? So if I erase this and put a negative theta, and I erase this, and I just put a negative theta in here, and a negative theta in here, what I want to do is think about how can I take what I just found here, plug it in there, and simplify and come up with something. Well, basically, we know that the cosine of negative theta right here tells me that's the same as the cosine of theta. So I can erase this and go back to the cosine of theta, and I can take this guy right here, the sine of negative theta, and I can basically pull the negative out in front. So let's get rid of that, okay? And I'll pull that out in front. So what does this tell me if I compare this one to the one I just had? So the tangent of theta, where it's the sine of theta over the cosine of theta, well, they're negatives of each other, right? So just like this first relationship. So we can say that the tangent of negative theta is equal to the negative of the tangent of theta. All right, so let me erase this. Using a similar thought process, we can get the ones for the reciprocals, okay? So basically the reciprocal of sine is cosecant, okay? So when you look at this, the signs are going to be the same, right? So basically it's the same property. So with this guy, let me put this down here in a different color. If I deal with cosecant, so cosecant of negative theta, it's equal to the negative of cosecant of theta, okay? With cosine, you have the reciprocal that's going to be secant, right? So I can do here, I'll drag this down here. Let me change my color. The secant of, let's say, negative theta will be equal to the secant of theta. Okay, so those match. Then lastly, this guy right here, let me change the color one more time. I think I'm running out of ink, so let me use this one. So here with the tangent, again, it's going to be, if you flip it, you get cotangent. So I'm going to say that the cotangent of negative theta is equal to the negative of the cotangent of theta. Okay, so these are the negative angle identities, or some books again call it the even odd identities because of when we're talking about even and odd functions. Now I want to pull up this little PDF which is attached at the beginning of this section for you. Okay, so I say keep this PDF handy. It's going to be very useful as a reference in this section. you want to start by just going back and forth and reading things and writing it out, okay? As you get really good at working with these identities, you're going to commit these to memory, okay? You're really going to need to do this before you get to calculus. So you have here the reciprocal identities, okay? We have here the quotient identities. We have here the Pythagorean identities, and then the negative angle identities, which we just talked about. So we're going to use this in this section. Together, these are all called the fundamental identities. And we're going to start by just solving a problem that we've already seen how to solve before. Okay, we're just going to do it in a different way. So we have the tangent of theta equals 3/4, and sine of theta is positive. Okay, so let's stop for a minute. This tells us we're where. Remember, the all students take calculus. So if I draw a little coordinate plane here, the all students take calculus. Okay, everything is positive in the first quadrant. In the second quadrant, it's sine and cosecant. In the third quadrant, it's tangent and cotangent. And in the fourth quadrant, it's cosine and secant, okay, in terms of what's positive. So here we have that tangent is positive and so is sine. So that means I have to be in quadrant 1. Okay, so before you do anything, let's just figure that out. And we're just going to put here that we're in quadrant 1, okay? So I want to find the secant of theta, the sine of theta, and the cotangent of negative theta. So let's start out with the secant of theta. How can we figure this out using identities? Well, let me pop this back open, and I want to look for a relationship between tangent and secant, okay? And I see that I have one here, tangent squared theta plus 1 equals secant squared theta. So let's go ahead and write this out. So we have that the tangent squared theta, then we have plus 1 is going to be equal to the secant squared theta. Okay, so remember, and this is going to come up later on when we're simplifying trigonometric expressions, this is the same as if I had tangent theta squared. Okay, this is just a different way to write this. So what I'm going to do is I'm going to plug in for what I have. So I'm going to plug in the 3/4 there. This is 3/4 and it's being squared. Okay, that's why I just showed you that. So let's erase this and put 3/4 here. And I'm going to square this guy, okay? And so if I square 3/4, I get 9/16. And let me scroll down to get some room going. We'll come back up and answer this. So this will be 9/16 plus 1. Now, to do anything here, I know I need to get a common denominator, so I might as well just write this as 16/16 and just go ahead and add. 9 plus 16 is 25. So this would be 25/16, okay? So this equals secant squared theta. Now, I want to get this guy, this secant of theta by itself, because that's what I'm told to find, right? I want to find secant of theta, not secant squared of theta. So to do this, I want to take the square root, okay? But I need to know which one to take, and I need to think about, okay, well, if I'm in quadrant 1, everything's going to be positive, okay? So I just want the principal square root. So I'm going to take the principal square root over here, and this guy over here will now be just secant of theta, okay? So here I can simplify and say, and I'm just going to flip this around and say the secant of theta is equal to the square root of 25 is 5 and the square root of 16 is 4. So this guy is going to be 5/4. Okay, so that's one way we can do it. Obviously, we saw earlier in the course that we could have done this a different way. Whichever way you want to do it, I'm just showing you different ways you can attack the same problem. So let's put this up here. Let's erase all this and let's just drag this up here and we'll attack the next part of that problem. So we have here, if we come up here, we want to find the sine of theta. Okay, so let's think about this. And there's a lot of different ways to do this. But again, if I go back to my little cheat sheet, I want you to see this quotient identity here where the tangent of theta, again, is the sine of theta over the cosine of theta. Now you might think, well, we don't have cosine of theta, but we do because of the reciprocal identities. We just found the secant of theta, which is 1 over the cosine of theta. Okay, so let's go ahead and put this down here. I'm going to first just write the relationship that the tangent of theta is equal to the sine of theta over the cosine of theta, okay? And the cosine of theta is 1 over, so it's 1 over the secant of theta, okay? So you know you can flip this, and you would basically have the secant of theta, okay, times the sine of theta, but I want to solve for this guy, so I'm going to divide both sides by the secant of theta, and that's going to give me the sine of theta by itself. Now, all I have to do is plug in the information I'm given. So I have for the tangent of theta, 3/4. So I have 3/4. For the secant of theta, I just found that was 5/4. Okay. So basically what I'm going to do here is say, and let me scroll down and get some room going. I'll come back up. I have 3/4 times, I'm going to flip this because I'm dividing fractions. So 4/5 we can see that this is going to cancel, and I'm left with 3/5. So that's going to be my sine of theta. So let's go ahead and put this over here and say that my sine of theta is equal to 3/5. Okay, for the last part of this problem, we're asked to find the cotangent of negative theta. So the cotangent of negative theta, okay, let's just pop open this guy again. We can see the cotangent of theta is 1 over the tangent of theta, okay? So I could say this is 1 over the tangent. In this case, I have a negative theta, so negative theta, okay? And then from here, I'm given that the tangent of theta is 3/4, but I want the negative of that. Remember, you can pull this out. We saw that earlier. So you might as well say that this guy is going to be equal to 1 over the negative of 3/4, okay? So to finish this up, I'm just going to flip this and say that the cotangent of negative theta is going to be equal to the negative of, again, flip this guy, it would be 4/3. So those are going to be your answers here, okay? You're going to have the secant of theta is 5/4, the sine of theta is 3/5, and the cotangent of negative theta is negative 4/3. All right, so the next thing we want to do is we want to write one trigonometric function in terms of another. So you're going to see this in your book. Let's say you see something like the cosine of theta, and you're asked to write this in terms of, okay, so in terms of the tangent of theta, okay? So how can we do this? Well, the first thing you want to do is you want to find an identity that's going to work, where it's going to relate your trigonometric function, which in this case is the cosine of theta, to the tangent of theta. So if we go back here, I'm going to pick this Pythagorean identity here. So I'm going to pick this guy, which involves the tangent of theta, okay, and the secant of theta. So what we're going to do, let's go ahead and minimize this. I'm going to go to the next page. I've already written it down. So we have 1 plus the tangent squared of theta is equal to secant squared of theta. Remember, when you think about the secant of theta, it's 1 over the cosine of theta, okay? So what I'm going to do first is just take the reciprocal of each side. So I'm going to say this is 1 over 1 plus tangent squared theta is equal to 1 over secant squared theta, okay? So now I'm going to replace. I know that this guy right here, again, because of the reciprocal identities, is going to be cosine squared theta, okay? So I'm going to replace this. On the left, I'm going to say 1 over 1 plus tangent squared theta is equal to, on the right, I'm just going to put cosine squared theta. Now, I want this in terms of cosine of theta, okay? So I'm going to take the square root of these sides here. On this side, I want plus or minus because I'm not given a quadrant, okay? So I don't know any information about what quadrant I'm in. So I'm going to write this. Let me change the color here. I'm going to put cosine of theta is equal to plus or minus the square root of this whole thing. So 1 over, you've got 1 plus your tangent squared theta, okay? So from here, we know that we can take this and make it a 1. So let's go ahead and say cosine of theta is equal to, I'm going to go plus or minus this 1 up here, over, down here I'll have the square root of 1 plus the tangent squared theta. Okay, so we want to always rationalize our denominator. So to do that, let me scroll down and get some more room going. I'm going to multiply this by the square root of this guy, so 1 plus your tangent squared theta over square root of 1 plus your tangent squared theta. Okay, so that's just going to rationalize the denominator. So I'm going to have cosine of theta is equal to, so this guy right here, I'm just going to have plus or minus. Remember, 1 times anything is just itself, so I'll have the square root of 1 plus tangent squared theta over, this times this would give me the radicand there, so 1 plus tangent squared theta. Okay, and we're done. So that's the exercise here. It's just meant to give you some practice writing one trigonometric function in terms of another. Okay, so now let's move into actually simplifying, okay? And I think you'll find that once you get started on simplifying and writing things in terms of other things, at first it's a bit challenging, but really once you practice enough, this becomes really, really easy. So we have the secant of theta times the cotangent of theta times the sine of theta. So when you get a problem like this, you want to think about putting your expression in terms of sine and cosine, okay? And if you have sine or cosine in your expression that you're trying to simplify, leave it alone. Don't try to mess with that, okay? You want to mess with everything else. So I'm going to leave this as it is, and I'm going to change this one and this one. So because there's multiplication here, when I go back, I'm going to be thinking about my reciprocal identities, okay? So I'm going to be using these guys here to simplify. So basically, the secant of theta is 1 over the cosine of theta, okay? The cotangent of theta, I know, is found by flipping the tangent of theta. So it's going to be the cosine of theta over the sine of theta, okay, over the sine of theta. And then this is times this sine of theta. So you see that when you plug these things in, a lot of stuff's going to cancel. So this cancels with this cancels with this, and I'm basically just left with 1. Okay, so this is pretty common. When you just see multiplication like this, if you have sine or cosine, leave it alone. Okay, the other stuff is what you want to plug in for and try to see what you can get to cancel. Now, let's take a look at another example where we're simplifying a trigonometric expression. This one is going to be problematic for a lot of beginners because of the notation here. So I want to make sure you understand the notation. So when we work with, again, something like sine squared theta, remember this is the same thing as if I said sine of theta being squared like this. It's very important you understand that. When you look at this guy right here, the temptation, because of sine of negative theta, okay, is equal to the negative of the sine of theta, the temptation here is to do what? It's to go the negative sine squared theta, okay? That's not actually accurate, okay? You have to think about it like this guy right here, okay? So the way I want to write this is I want to make it crystal clear what's going on, and I want to say that I have the sine of negative theta, okay, this guy being squared, okay, the whole thing being squared. Then plus, I'm going to do the same thing here. So I'm going to have the tangent of this negative theta, okay, this guy right here being squared. Then plus, I'm going to have the cosine of this negative theta being squared, okay, the whole thing being squared. So now it's crystal clear, okay, when I pull this negative out, what's going to happen? We're going to have the negative of sine of theta, but the thing is squared, plus, pull this out, okay, I'm going to have the negative of the tangent of theta, and I don't need parentheses in that case, okay, and then this guy's going to be squared, and then plus, in this case, you don't need to pull anything out because the cosine of negative theta is equal to cosine of theta, okay, so I can just say this is the cosine of theta being squared, okay. So now I want you to see what I'm getting at here. Basically, if you had incorrectly pulled that out and said you had the negative of sine squared theta, you would get the wrong answer, okay? Because this guy right here, because you're squaring the negative, it becomes positive, right? So this is going to go away. So you get rid of that, and you basically go back to having sine squared theta. Not the negative of sine squared theta, sine squared theta, okay? Because this negative got squared. Same thing here. This negative is going to get squared. So plus tangent squared theta. Then plus, you have your cosine squared theta. Okay, so from here, that's the first step, just to understand where you're going there. But from here, you want to realize that if you're dealing with something that's squares here and you've got pluses and minuses involved, not in every case, but usually you want to look at the Pythagorean identities. So if we pop these open, you see that sine squared theta plus cosine squared theta is 1. So that's the first thing I'm going to do. You can consider this plus this to be 1. You can reorder this if you want to make it crystal clear. So we'll say sine squared theta plus your cosine squared theta plus your tangent squared theta, okay? This guy right here is equal to 1, okay? We just saw that. So I'm just going to substitute. So I'm going to put in here a 1 plus the tangent squared theta. Now, can we make this simpler? Let's go back and see if there's anything that involves tangent squared theta and 1. Yes, right here. Tangent squared theta plus 1 is equal to secant squared theta. So I can replace this with just secant squared theta. Okay, and that's going to be my answer. And you can see how we really simplify this down to just one of these guys. In this lesson, we want to talk about verifying trigonometric identities. All right, so in this particular section, you might struggle a little bit when you first get to it. It's a topic that you really need a lot of practice with. It's not as straightforward as other topics where you have a set list of things that you need to do, okay? If you were solving basic equations, I could give you the steps and you could perform those steps and basically you would get the right answer all the time. With this, there are just hints or strategies you can use to arrive at the correct answer, but it's not so clear in terms of what you need to do, and there's also multiple ways to do the same thing. okay? So I have some little tips here for you, and they're standard from any textbook, okay? So you'll get this in any textbook. The first thing is to memorize the fundamental identities. So again, in the last lesson, we talked about these fundamental identities, and we talked about simplifying trigonometric expressions using the fundamental identities. Again, we looked at a little handout here, so hopefully you have that again, and you want to memorize these. So you have the reciprocal identities, you have the quotient identities, the Pythagorean identities, and then you have your negative angle, or again, some books call this even odd identities. So all of these are going to play a crucial role when you're verifying these trigonometric identities, okay? So here are some other tips. You always want to try to work on the more complicated side, okay? So when you're verifying trigonometric identities, you're not going to be doing the same thing as when you solved equations. When you work with equations, you might multiply both sides by the same number or add the same term to both sides, something like that. Here, you're not going to do that. You're going to work on one side, generally speaking, the more complicated side, and try to make it match the other side, the simpler side, okay? Another tip is sometimes you'll want to express everything in terms of sine and cosine. That doesn't always work, but it's just a general tip, okay? You want to perform any indicated algebraic operations such as factoring or expanding. Here, you want to think about all those special product formulas, okay, and all the special factoring formulas. Those are going to come up a lot. And then we have use the formula for multiplying conjugates. So remember, if you have 1 plus sine of x times 1 minus sine of x, this is going to be 1 squared, which is 1, and then minus sine squared x. So basically 1 minus sine squared x, and we know from our Pythagorean identities, this is going to be exactly equal to cosine squared x. Similarly here, I could make this 1 minus cosine squared x, okay? And that's going to be exactly equal to sine squared x. Okay, so let's take a look at the first example. And the first few of these are going to be really, really easy. So go ahead and pause the video and try them on your own once I kind of get going here, and then see the solution. So the first thing is I'm going to think about which side is simpler. So to me, this side is simpler, okay? So I'm going to try to work on this side on the left. Now, pretty much every book that you're going to see has different formatting. Generally speaking, they sometimes will take this guy right here and just work on the more complicated side, and at the end, they'll show you that it matches. What I'm going to do here is I'm just going to take this guy and flip it. So I'm just going to say I have 1 plus sine of x is equal to, over here I'm going to have cosine of x plus cotangent of x, okay, over the cotangent of x. I'm flipping it because what I'm going to do is modify the right and leave the left alone. Okay, so that's generally the formatting you're going to see. If your teacher tells you to do something else, then follow that. Okay, so what I'm going to do is just put equals over here. I'm not going to mess with this. My goal is to get this side right here to match this 1 plus sine of x. So the first thing I'm going to do is I'm going to write things in terms of sine and cosine. So I have cosine here, okay, so I'm not going to touch that. But cotangent of x, again, if you think about the reciprocal identities, it's cosine of x over sine of x. So I'm going to start by saying I have cosine of x plus cosine of x over sine of x. And this is over, again, if I have cotangent of x, I'm going to write it as cosine of x over sine of x. Okay, let's scroll down and get some room. We'll come back up when we get to a stopping point, okay? So what I want to do here is think about the fact that I have basically a complex fraction, right? So how do you simplify that? You look at the denominator, so I have sine of x and sine of x. So if I multiply this by sine of x over sine of x, basically I'm going to distribute this here and here, okay, and I'm going to distribute this here. So I'm just going to keep my equals over here, okay? We might need more room, so let me just kind of slide this down a little bit. Sine of x times cosine of x is just sine of x times cosine of x. Then plus sine of x here would cancel with sine of x here, so I just have cosine of x here, okay? Then down here, this sine of x here would cancel with this sine of x here, so I'm going to put this over just the cosine of x. Okay, so let's go down a little bit more, and let's think about something here. We have the cosine of x and the cosine of x. What operation could I do there? Well, I could factor, right? So I'm going to put equals here, and I'm going to pull that guy out, okay? So I'm going to say I have the cosine of x. Inside the parentheses, I'll have the sine of x, okay? Plus, if I pull this out, I have a 1, okay? Then this is over the cosine of x. And now what I'm going to do is I'm going to cancel this with this. And what I'm left with is going to be the sine of x plus 1, okay? If we go all the way back up, we see here that we have 1 plus sine of x. And here we have sine of x plus 1, right? So I could write this as 1 plus sine of x, okay? And then I'm just going to put a big check mark here to show that this right side now here matches the left side, okay? So you could have gone about this a different way. There's multiple ways to verify a trigonometric identity. The main thing is, again, start with the more complicated side, work your way down, okay, and try to make it match the other side. Okay, so once you've found that it matches, you're done. Put your check mark and move on. Try to make your steps as clear as possible so that whoever is grading it can give you full credit. Okay, let's take a look at another example. This is another kind of easy one. So we have the cotangent of theta over sine squared theta equals cosecant squared theta over tangent of theta. Now, in this particular case, both sides are equally complex. So I'm just going to leave the left one alone because it already contains sine, okay? If you wanted to do it a different way, again, that's fine. So I'm just going to basically put equals here, and I'm going to manipulate this in terms of sine and cosine. So cosecant, okay, if I think about the reciprocal identities, is 1 over sine, okay? So basically, I can say cosecant squared of theta is 1 over sine squared of theta, okay? And then over tangent of theta is going to be my sine of theta over my cosine of theta, okay? So what I want to do here, think about the fact that you are basically going to flip this guy, okay? Basically, if you're going to divide fractions, you multiply the first fraction by the reciprocal of the second guy, okay? So let's scroll down a little bit. And I'm going to go 1 over sine squared theta times, this is going to flip, so it's going to be cosine of theta over sine of theta, okay? And can anything cancel here? Well, no, you might be expecting to cancel sine of theta. So at this point, you might stop and say, well, what's going on? So let's go back up here, okay? Let's think about what we have. We have cotangent of theta over sine squared theta. Well, I have sine squared theta here. This right here, if you really think about your reciprocal identities, remember cosine of theta over sine of theta is cotangent of theta. So I can replace that, okay, I can replace that with cotangent of theta, okay, so I can put 1 over sine squared theta like this, multiply it by cotangent of theta, okay, and basically we're done, right? All we have to do is multiply this through and say I have the cotangent of theta over sine squared theta, okay, so now your left side and your right side are going to match, so you put your check mark there. Again, just make sure you show your steps so your teacher can give you full credit. All right, for the next one, we have the negative of cosecant squared theta times cosine squared theta is equal to 1 minus cosecant squared theta. So for this guy, you might be thinking that the right side is a bit more complicated. It looks kind of like the difference of squares, right? So it is, actually. You could factor that if you wanted to. But I'm not going to do that. I'm going to leave this side alone. Whenever I see something that looks like this, I'm thinking about the Pythagorean identities. I have a minus or a plus with a 1 here, and this is squared. If I look at my little handout here, I want you to think about this one right here. So 1 plus cotangent squared theta is equal to cosecant squared theta, okay? So we'll come back to that in a moment. And I'm just going to work through this. I'm going to flip the sides here. I'm going to put 1 minus cosecant squared theta, okay, is equal to, I'm going to put negative cosecant squared theta times the cosine squared theta, okay? So what I'm going to do first is just take this side right here and express it in terms of sine and cosine. Again, for a lot of these problems, that ends up being all you really need to do to end up with a solution. So I'm going to put equals over here. I'm going to change this. I'm going to put my negative out in front. Cosecant squared theta, again, with the reciprocal identities, I can put 1 over sine squared theta, okay? This is times cosine squared theta. And then over here, I have the negative of, I'll say, cosine squared theta over sine squared theta. Can I make a replacement here? Yes, because this guy right here is the cotangent of theta, right? So basically what I have, let me scroll down a little bit, is the negative of the cotangent squared theta. Now, can I do anything with this? Remember, I talked about this Pythagorean identity here, okay? Let's assume I moved this over here and this over here. So basically I would have 1 minus the cosecant squared of theta is equal to the negative of cotangent squared theta. So right now I have the negative of cotangent squared theta, and I can replace it with exactly this right here, 1 minus cosecant squared theta. Okay, so that's what I'm going to do. So I'm going to say this guy right here is 1 minus the cosecant squared theta. Okay, so now my left side exactly matches my right side. I'm going to put my check mark there, and I'm done. All right, let's take a look at a harder example. So here we have 2 times the tangent of theta times the secant of theta is equal to 1 over 1 minus the sine of theta minus 1 over 1 plus the sine of theta. So when you see this guy right here or this guy right here, you got to be thinking about conjugates, okay? So I'm definitely going to leave the left side alone, and I'm just going to play with this right side. Before I do anything, I just want to do this off to the side so I have a lot of room to work. I know that I would want to get a common denominator here. Okay, so how would I do that? Again, I'm thinking about conjugates. So here I would multiply by 1 plus the sine of theta. Okay, here 1 plus the sine of theta to make that legal. Again, this is 1. I can multiply these together. So you see how this formula is going to work. If you had a minus b, that quantity, times a plus b, this quantity. Remember, this is a squared, first guy squared, minus b squared, minus the second guy squared. Okay, in this case, it's going to be no different. This is going to end up being 1, the first guy squared, then minus, you have sine squared theta, so sine squared theta, this second guy squared, okay? So up here, this would just be 1 plus sine of theta, okay? You can get rid of this, and then down here, this is going to be 1, you don't need 1 squared, minus the sine squared theta. Okay, so that's going to be this part right here. For this part right here, I have a plus here, so basically, this part is going to be a minus. So I'm going to put a minus here, and I'm going to end up with what? 1 minus sine of theta in the numerator, because again, I'm going to multiply by 1 minus sine of theta here, and 1 minus sine of theta here, and then down here it's the same thing, right? It's the same thing, so it's going to be 1 minus sine squared theta, okay? So let me erase this, and let me slide this over so I get my formatting right. Slide this over just a little bit, put equals there, and again, I can write this with a common denominator, so you can even do this real quick right here so we save a little bit of time and a little bit of effort. So let me just put 1 minus sine squared theta like this, and then I'll put this as 1 numerator with a minus here, but be very, very careful. When you're subtracting this away, you're subtracting away the whole thing. So go ahead and wrap that in parentheses to remind you that you need to change your signs because you're subtracting the whole thing away. Okay, so let's keep going and see what's going to happen here. So I'm going to have 1 plus sine of theta. Again, you're distributing this negative. So minus 1, distribute the negative here, so plus sine of theta, okay? And this is over 1 minus sine squared theta. So what can we do here? Well, we see immediately that this is going to cancel, okay? So now I basically have 2 times sine of theta. So 2 times sine of theta over 1 minus sine squared theta. Now, remember in the hints, we saw that 1 minus sine squared theta was cosine squared theta. Again, if you go back to this, if you have this guy right here and you just subtract this away, so 1 minus sine squared of theta would give you cosine squared theta. So if we come back here, I can replace this with cosine squared theta. So let's go ahead and do that. So I'm going to put equals 2 times sine of theta over the cosine squared theta, okay? Now, is this getting close to what we want? Let's go back up and see where we are. We have 2 times the tangent of theta times the secant of theta. So are we close to that? Well, I see I have the 2. I need the tangent of theta and the secant of theta. So to get this, I'm going to break this up. Remember, cosine squared theta can be written as cosine of theta times cosine of theta, okay? It's just this times this gives me cosine squared theta. Now, up here I have 2 times sine of theta. Now think about it, if I have sine of theta over cosine of theta, that's the tangent of theta, okay? And if I have 1 over cosine of theta, that's the secant of theta. So I already have what I need, okay? You just need to break things up so you realize what's going on. So I'm going to put this as 2 times sine of theta over cosine of theta times 1 over cosine of theta. And then I'm just going to, again, replace this with what I'm looking for. So in this particular case, it's going to be what? 2 times, this is going to be the tangent of theta times, in this case, this is going to be the secant of theta. And now the left side and the right side perfectly match. So I'm going to go ahead and put my check mark there. And again, I'm done. All right, let's take a look at one final problem. And this guy's going to be pretty challenging overall. So I encourage you to pause the video and try this on your own. But before you do so, I want to just give you a little hint that you basically want to get both of these to a common expression. Okay, so you want to work on one side, get it down to in terms of sine and cosine. This side is pretty hard if you are not used to working with these. This side's pretty easy. Okay, so you want to get it to this common third expression. So go ahead and pause the video and try it. And hopefully you did give that a try. And I'm just going to start with the left-hand side here, okay? So I'm going to start by just taking this guy and trying to write it in terms of sine and cosine. So how can I do that? Well, let's start out by just putting that we're working on the left-hand side. Okay, some teachers want you to do this. Others don't care, so just get with your teacher. And I'm going to first copy the left-hand side. So I have the secant of x plus the tangent of x over the secant of x minus the tangent of x. Now, lots of ways to do this. I'm going to go through one that is probably not obvious if you haven't worked a lot of these problems. Remember, the secant of x, by definition, is equal to 1 over the cosine of x, okay? So if I multiplied this secant of x, which is 1 over the cosine of x, times the cosine of x, I would get 1, okay? So in other words, if I did this guy right here, let me just copy this real quick. So secant of x plus the tangent of x over the secant of x minus the tangent of x. If I multiply this guy by the cosine of x over the cosine of x, when I distribute this here, this is going to be 1. When I distribute this here, this is going to be 1. Another benefit is when I distribute this here and this here, think about the fact that the tangent of x is the sine of x over the cosine of x. So the cosine of x is going to cancel in each case. So I'm going to end up with 1 plus the sine of x and 1 minus the sine of x. So that's pretty simple, okay? So that's how I'm choosing to do this. Again, you could arrive at this a different way. So let me just put equals over here. This multiplied by this is going to give me 1, okay? And then plus, let me just write this out. So the tangent of x times the cosine of x. We know we can cancel that further. And then we have, again, cosine of x times secant of x is 1 minus, we'll have the tangent of x times the cosine of x. Okay, so from here, I'm going to, again, keep simplifying. Let's put 1 plus, I'm going to do sine of x over cosine of x times the cosine of x. Again, this is going to cancel. So this cancels with this. And this is over. Let me get some more room here. I think I'm going to run out. So we have 1 minus, again, I'm going to write this as the sine of x over the cosine of x times the cosine of x, okay? So this is going to cancel, and I have the sine of x there, okay? So let's just write this one more time. We'll put 1 plus the sine of x over 1 minus the sine of x. So that's pretty simple. It's in terms of sine, okay? And basically, now what I want to do is try to get the right-hand side to match this, and you're going to find that that's pretty simple. So let me start a new sheet here. And I'm going to say the right-hand side. Okay, and let me make that a little bit better. So let me put the right, and I'm going to try carefully to write this. So right-hand side. Okay, penmanship is hard for me. So let's come back up, and let's think about this guy. So we have 1 plus 2 times the sine of x plus sine squared of x over cosine squared of x. So let's come down. So we have 1 plus 2 times the sine of x plus sine squared of x, okay, over, we're going to have the cosine squared of x. So the first thing is, you should be thinking about factoring when you see this pattern. Again, this is basically where you have x plus y quantity squared, right? It becomes x squared, so first guy squared, plus 2 times the first guy times the second guy, so 2 times xy, plus the last guy squared, okay? That is exactly the pattern you have here. This is going to be basically 1 plus sine, okay, of x, quantity squared. So I'm going to take this guy, and let me do this properly. So let me just kind of slide this down a little bit, okay? I'm going to put equals. So I'm just going to say this is 1 plus the sine of x, quantity squared, over your cosine squared of x, okay? So I'm going to put equals over here. So what am I going to do with this now that I've factored it? Well, again, if you see something like cosine squared of x, and you see something in terms of sine of x, I want you to think about the fact that this can be replaced with 1 minus sine squared of x, okay? So I'm going to write this as 1 plus sine of x, quantity squared, over, this is going to be 1 minus sine squared x. So at this point, some of you are thinking that there's something weird going on. This doesn't match this, but it will in a second. This is the difference of squares, so you need another factoring pattern here. This is 1 squared, basically, minus sine squared x. So I'm going to rewrite this, and then it's going to be completely obvious what's going on, okay? So first, let's go ahead and write this as 1 plus sine of x times 1 plus sine of x. Okay, so I'm just expanding this. Nothing illegal about that. I have an exponent of 2 there, so I'm allowed to do that. Okay, then down here, I'm going to factor this as 1 plus sine of x times 1 minus sine of x. And now it is completely clear what I'm doing. Okay, so this cancels with this, and I have 1 plus sine of x over 1 minus sine of x. Again, if we go back, what did we have here for our left-hand side when we worked it? 1 plus sine of x over 1 minus sine of x. So what I'm going to do here, I'll just put equals 1 plus sine of x over 1 minus sine of x. And to complete this guy, you might just want to write your basically 3 expressions here. So I'm going to say that the secant of x plus the tangent of x, so plus the tangent of x over, and I don't know if I can fit this all on the screen, but I'm going to try. So the secant of x minus the tangent of x, let me scroll this down and try to write smaller, is equal to, we have this 1 plus the sine of x over 1 minus the sine of x. So this is what we found from working the left side and the right side. Okay, so this is your basically your common third expression. Okay, and this is going to be your 1 plus your 2 times sine of x plus sine squared of x. Let me see if I can scooch this down just a little bit more. And then over, you had your cosine squared of x. Okay. So this is going to basically do it for this guy. Again, you're not going to probably see too many of these if you're on a basic test. You're probably going to get maybe one of them towards the end. They realize how much time these guys take, okay? So if you get something where you're just working and working and working on one side, you can't get it anywhere, go ahead and get it in terms of sine or cosine, stop, and then start working the other side. See if you can get it to match. In this lesson, we want to talk about the sum and difference identities for cosine. All right, so let's start out by looking at the sum identity for cosine. So let's say you had the cosine of some angle A plus some other angle B. This is equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. So let me give you a quick example. We're going to work on examples like this in a little while, but just so you see what's going on, let's say you had the cosine of, let's say, 45 degrees plus 30 degrees. So we know this is the same as if you added those two angles and you said you wanted the cosine of 75 degrees. But you can break this up if you wanted to get an exact value, and I'll talk more about that in a little while. But basically, if you wanted to do this, it's the cosine of the first guy, so the cosine of 45 degrees, then times the cosine of the second guy, so times the cosine of 30 degrees, then minus the sine of the first guy, so the sine of 45 degrees, and then times the sine of the last guy or the second guy, which is 30 degrees. So this is how you would have to set this up. A lot of people incorrectly say this is the cosine of 45 degrees plus the cosine of 30 degrees. That does not work. Okay, so you can't do that. You have to use this formula. Now for the other guy, let's say you have the cosine of A minus B. What's going to change is the sign here. So I always remember this is the opposite sign. Cosine of A times cosine of B, now plus sine of A times sine of B. So for example, if you did the cosine of 45 degrees minus 30 degrees, well, now I'm looking for the cosine of 15 degrees, and it's still cosine of 45 degrees times cosine of 30 degrees. This is now going to change to a plus the sine of 45 degrees times the sine of 30 degrees. So it's just a change in the sign. So this sign and this sign will always be different. Now, let me get rid of this, and let's talk about where this guy comes from. What you'd want to do is draw yourself a little unit circle on a piece of paper. And so, again, this point right here, we know the x-coordinate would be 1 and the y-coordinate would be 0. Again, we're on the unit circle. If you went around and labeled these points, this would be 0, 1. Then this point right here would be -1, 0. And then lastly, this point down here, this would be 0, -1. So again, we're on the unit circle. So we know if we're on the unit circle, and let's say starting here and going to here, I have this arc with length t. Well, then I know the coordinates for this point q sub 1. The x value is the cosine of t, and the y value is the sine of t. Now, if I keep going, and let's say I end up at this point right here, p sub 1, well, now I have an arc that has a length of t plus s, or you could say s plus t. So the x value here for this point is the cosine of s plus t, and the y value here is the sine of s plus t. And then if I come this way, notice that I'm rotating clockwise. So here I would say this is negative s. So whatever this is right here, it's the negative of that. And so if I look at this point q sub 0, the x value here is the cosine of negative s, and the y value here is the sine of negative s. Now, using the negative angle identities, you can really say that this is the cosine of s, because the cosine of negative theta is the same thing as the cosine of theta. And then you can say that this is the negative of the sine of s, because again, if you have the sine of negative theta, it's equal to the negative of the sine of theta. So we're going to be using this right here instead of this right here. All right, so we have that settled. And now what we want to move into is we want to identify that we have these two equal arcs. So hopefully you can see this. The arc length, if I think about here to here, so this has s and it has t, would be the same as if I consider, let me change my color here, from here to here, right? Forget about the fact that this is negative s. Again, this guy and this guy in terms of the arc length, it's going to be the same. So you have s plus t, and here you have s plus t. So let me draw this out so that nobody's lost. And probably I should change the color again. Let me use this like red here. So let me trace this as good as I can. So this arc here would be equal to this arc here. And I'm going to go underneath a little bit like that. Okay, so we can see that those two arcs are equal. And when you have equal arcs, they are what we call subtended by equal chords. So this chord here and this chord here, these two are going to be equal, right? So you see up here, I've written that the distance from p sub 0 to p sub 1, so that's this right here, is equal to the distance from q sub 0 to q sub 1. Okay, so that's this distance right here. So I went ahead and already set everything up for us. So what you would want to do from this point is write out your distance formula. Remember, we're on a coordinate plane, and if we want to find the distance between 2 points, we say the distance is equal to the square root of, you have x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. Now what I did was I went ahead and squared both sides of this. So I'm working with the distance squared now. So I'm saying the distance between the point p sub 0 and p sub 1, that guy squared, is equal to the distance between the point q sub 0 and q sub 1, that guy squared. So what we're going to do is just work on one side at a time, and then I'm going to set these two guys equal to each other, and you'll see you have your formula. So first off, I have, again, the distance squared here, and I have my 2 points. So let me write this out. I'm not going to write the distance squared equals. We don't even need that. I'm just going to plug in here. So I'm going to consider p sub 1 as my second point, and p sub 0 as my first point. So let me get the x coordinate here. So this would be the cosine of this s plus t. And then this guy right here would be minus, you would want your 1 here. Okay, so I took the x coordinate here and the x coordinate here. Let me wrap that and square it. Then we have plus. So now I'm working with the y's. So the y from this second guy here, so that's going to be your sine of this s plus t. And then we would have minus, your y here is 0. So let's just write it in for right now, but it's going to go away in a second. So that's just setting this up. Again, exactly matching this. I didn't write the d squared equals, but we really don't need that. So I'm just going to say this equals here. So I'm going to use my formula. Remember, if you have, let me just get rid of this for a second so I can write this out. So x minus y quantity squared. This is x squared minus 2xy plus y squared. So we're just going to use that formula. Pretty easy. So I'm just going to say I have this first guy squared. So cosine squared. And then the angle would be s plus t there. And then minus 2 times this times this. Now 2 times 1 is 2. So it's just 2 times the cosine of this s plus t here. And then plus this last guy, 1 squared, which is just 1. Now I'm going to go plus. Now this one right here, because you have minus 0, you could really just get rid of this and just say you have sine of s plus t being squared. So I'm just going to write that as sine squared of this s plus t angle. So now we have cosine squared of s plus t, and we have sine squared of s plus t. Remember, if the angle is the same, which we have s plus t and s plus t, well then cosine squared theta plus sine squared theta is equal to 1. So this plus this would give me 1. So really I can say that we would have 1, and then we have minus 2 times the cosine of this s plus t, and then plus 1. So this is going to give me a final result for this side. 1 plus 1 is 2. So we'll say 2 minus 2 times the cosine of s plus t. Okay, let me grab this, and I'm just going to paste this in here. So this is one side. Let me put equals, and now we're going to work on this side. So we have q sub 0 and we have q sub 1. So just plug in here, forget about the d squared equals. I'm just going to find the x sub 2, which again, I'm labeling this as the second point. So I want cosine of t. So then minus, you want your x sub 1. Here that would be cosine of s. Let me close that down and square it. So then plus, you have your y sub 2. So here that's going to be the sine of t. So the sine of t. And then you have minus your y sub 1. In this case, that's going to be the negative of the sine of s. Now, minus a negative is plus a positive. So you want to put a plus there, and then the sine of s. So be very careful about that step there. A lot of people get confused. Remember, this is right here a minus, and in the formula you have a minus. So minus a negative is plus a positive. That's why we have a plus there. Okay, so I'm just going to use my formula here. So we know the formula for this one. In this one, if you have x plus y quantity squared, it's x squared plus 2xy plus y squared. Okay, if this changes to a minus, then only this changes to a minus. Everything else is the same. Okay, so let's get rid of this, and let's write equals here. So this would be the first guy squared, which is cosine squared t, and then minus 2 times this guy times this guy. So the cosine of t times the cosine of s, and then plus the last guy squared. So this is cosine squared s. Okay, then plus, let's work on this guy. Now notice this is a plus guy here, right? So we have to think about a different formula. So the first guy squared, so sine squared t, then plus 2 times, again, the first guy times the second guy. So we'll put the sine of t times the sine of s, and then plus the last guy squared. So this is sine squared s. Okay, so once again, we have a situation where we can use that Pythagorean identity, sine squared theta plus cosine squared theta equals 1. So cosine squared t, and then sine squared t, so that's going to be 1. And then let me highlight this in a different color. You also have cosine squared s and sine squared s. Okay, let's put equals. So we have cosine squared t plus sine squared t. As I just mentioned, that would be 1. And then let's go ahead and say cosine squared s plus sine squared s. Let's just put plus 1 for right now. And then we'll go minus 2 times the cosine of t times the cosine of s, and then plus 2 times the sine of t times the sine of s. So we know that 1 plus 1 would be 2. So instead of actually making a new line, I'll just get rid of this and put a 2 here. That way we can speed this up. So I'm going to grab this, and I'm going to paste this in here. It doesn't quite fit on one line, so we know that this is equal to this. What I would do, let me actually drag this a little bit further down. I am going to subtract 2 away from each side of this equation. So this right here is going to cancel, and this is going to cancel. So let me see if I can write it in one line now. So negative 2 times the cosine of s plus t is equal to negative 2. I'm going to flip the order here for the purposes of the formula. You know that you can multiply in any order. So I'm going to say this is times the cosine of s times the cosine of t. Then plus, let me slide this down and see if I can fit this. We're going to say 2 times your sine of s. Again, I'm flipping the order for the formula, times the sine of t. Let's come down here a little bit. So what I'm going to do now is just divide everything by negative 2. And that's going to get us where we need to go. So this is going to cancel, and you'll have cosine of s plus t is equal to, this is going to cancel. So you have the cosine of s times the cosine of t. Remember, it's the cosine of the first guy times the cosine of the second guy. Then positive over negative is going to be negative, right? You can think about this canceling with this and giving you a negative 1. So you basically divide it by negative 1 or multiply by negative 1, whatever you want to think about there. But essentially you have a minus here, and then it's going to be the sine of s times the sine of t. So again, your sign is different. You have a plus here and a minus here, and then it's the sine of the first guy times the sine of the second guy. If we grab this and we go back to our original formula, you see that it matches. The only thing that's changed is the angle. Here we used A and B, here we used S and T. So let me actually get rid of this, and I'm going to show you where the second one comes from. It's very easy if you understand the negative angle identities. So let's say you said you had the cosine of A minus B, but you wrote it as A plus negative B, like this. So just following this formula here, you would have the cosine of A, then times the cosine of this negative B. Then you would have minus the sine of this A times the sine of this negative B. With negative angle identities, again, the cosine of negative theta is the same thing as the cosine of theta. And then the sine of negative theta is the same as the negative of the sine of theta. So what I can do here is just say this is the cosine of A times the cosine of B. So that matches this part right here. Now, this is going to come out, right? Because again, this is the negative of the sine of B. So the negative times the negative would give me a positive. So I can say this is plus now. You would have the sine of A times the sine of B. So that's where this formula is coming from. Now, let's look at a little example. And here we're given the cosine of 75 degrees. So this type of example, you're meant to give an exact value, okay? So the way you're going to do this is you're going to break 75 degrees up into two angles that's going to be on the unit circle, okay, where you're going to know what this cosine value is going to be. So I can break this up. One way to do it would be 45 degrees and 30 degrees. So I'll just say this is equal to the cosine of, and I'm just going to go 45 degrees plus 30 degrees, okay? And then I'm just going to use my little formula. So we'll have what? You want the cosine of this guy, so the cosine of 45 degrees times the cosine of this guy, the 30 degrees. Remember, your sine is going to alternate. So because in this particular case, we have a plus, we want a minus there. Okay, so you want to change your sign. And then now I want to go with the sine of these two angles. So the sine of 45 degrees, and then times the sine of 30 degrees, okay? So you're multiplying here, you're subtracting between the two, okay? So now what I want to do is just come through here and replace these with the actual values. So if you go to your unit circle and you go to 45 degrees or pi over 4 in terms of radians, you see that it's square root of 2 over 2 for the cosine, and then it's square root of 2 over 2 for the sine. Remember, this is the x, that's the cosine, this is the y, that's your sine. So square root of 2 over 2 in each case. So this is square root of 2 over 2, and this is square root of 2 over 2, okay? So what's going to be for 30 degrees? Let's go back. For 30 degrees or pi over 6 in terms of radians, you've got square root of 3 over 2 for your x or your cosine, and then 1/2 for your y or your sine. So this is going to be the square root of 3 over 2, and this is going to be 1/2, okay? So now all we have to do is just some basic arithmetic. So let's come down here a little bit, okay? And then let's switch the color here. So this would be the square root of 2 times the square root of 3. That would just be the square root of 6 over 2 times 2, which is 4. Then minus the square root of 2 times 1 is just the square root of 2, and then over 2 times 2, which is 4. Now, the only thing you can really do here is write this with a common denominator. So I'm just going to say that this is the square root of 6 minus the square root of 2. You can't combine there because the radicands are different, okay? You have the same index but different radicands, so you can't really combine those. So then this is over the common denominator 4, and this would be your exact value for the cosine of 75 degrees. All right, let's take a look at another example. So we're just trying to find the exact value again. So we have the cosine of pi over 12. So obviously this is given in terms of radians now. So what I'm going to do, and this is just a personal preference, I'm going to first convert this to degrees. It's a little bit easier for me to find two angles to add or subtract depending on what you want to do. So I'm going to multiply pi over 12 in terms of radians times 180 degrees over pi. And then basically I'm going to cancel this with this. 180 degrees divided by 12 would be 15 degrees, okay? So basically if I had 15 degrees, what I'd want to do is add and subtract. Let's say I did 45 degrees minus 30 degrees. That would give me 15 degrees, okay? So I could say this is the cosine of, if this is in terms of radians, 45 degrees is going to be pi over 4, okay? So pi over 4. And then minus 30 degrees is going to be pi over 6, okay, in terms of radians. So I'm just going to use my formula from here and just say that I have the cosine of pi over 4 times the cosine of pi over 6. Because this is minus, I now want a plus. So I'm going to do the sine of pi over 4 and then times the sine of pi over 6, okay? So let me put my equal sign there so we can keep going. And then I'll put equals over here. So if I think about pi over 4, or again, 45 degrees, I know the cosine of 45 degrees and the sine of 45 degrees, that's going to be the square root of 2 over 2 in each case. If I go back to my unit circle, you can see for 45 degrees or pi over 4 in terms of radians, we got square root of 2 over 2 and square root of 2 over 2. So let's go back and just replace this with the square root of 2 over 2 and the square root of 2 over 2. Now for pi over 6 or 30 degrees, we have again square root of 3 over 2 for the cosine and 1/2 for the sine. So this is going to be the square root of 3 over 2, and then we're going to have 1/2, and then I'm going to put a plus here between them. Okay, so let's go ahead and scroll down a little bit and do some arithmetic. So this would again be the square root of 6 over 4. Now plus, now I'm going to have the square root of 2 times 1, which is just the square root of 2, over 2 times 2, which is 4. Okay, so again, pretty much all we're going to do here is just write this with a common denominator. I can't add the square root of 6 and the square root of 2. I can't combine those radicals there because this and this is different, right? So you have different radicands, same index with different radicands. So I'm just going to write this as the square root of 6 plus the square root of 2 over the common denominator of 4. So this will be my cosine of pi over 12 radians. Okay, let's take a look at one more of these. So you might see the problem that we just worked on, those two problems, rearranged. So now you see the cosine of 83 degrees times the cosine of 38 degrees plus, this is the key here, the sine of 83 degrees times the sine of 38 degrees. So you see that you have the cosine of some angle times the cosine of some other angle, okay? And then you have the sine of that first angle, so the angles here match, and then the sine of that other angle. Okay, so the angles there match, you have a plus between them. You're meant to realize that you could write this as the cosine of, again, this is a plus, so I want a minus. So I'm going to do the 83 degrees minus the 38 degrees, okay? So what is this going to be? If I do 83 degrees minus 38 degrees, I'm going to get 45 degrees. So this is the cosine of 45 degrees. And we already know, because we've done this in the last two examples, that the cosine of 45 degrees is the square root of 2 over 2. So this is exactly equal to the square root of 2 over 2. All right, so another thing that comes up in this section, we're going to revisit the cofunction identities. So before, when we looked at something like the sine of theta is equal to the cosine of 90 degrees minus theta, we said that theta needed to be an acute angle. But now we're going to update that and say that theta can really be anything as long as the function is defined. So to prove this, what we're going to do is use the cosine difference identity. And over here, let me just put equals here. And I'm going to say that this is the cosine of 90 degrees and then times the cosine of theta. And then again, if this is a minus, you want to use a plus here. This is the sine of 90 degrees and then times your sine of theta. Now, we know that the cosine of 90 degrees is 0. And 0 times anything is 0. So you could write this out and say this is 0 times the cosine of theta. And then plus, we know the sine of 90 degrees is 1. So this is 1 times the sine of theta. And so again, this is going to go away. So you're just left with 1 times the sine of theta, which is just the sine of theta. So you can see that this is going to work for any value of theta. Again, as long as the function is defined, you'll be good to go. So we can actually extend this to these other guys that we looked at earlier. So we have the cosine of 90 degrees minus theta is equal to the sine of theta. The sine of 90 degrees minus theta is equal to the cosine of theta. Again, sine and cosine are cofunctions. Same thing for secant and cosecant, and for tangent and cotangent. Now let's look at a little example. And we haven't gotten to solving trigonometric equations yet. We should know that the solution I'm going to give you here is one of many possible solutions, or you could say an infinite number of solutions, but I'm just going to give you one. So here we have the sine of theta is equal to the cosine of negative 55 degrees. So what you'd want to do is write this left side in terms of cosine so that you have cosine of some angle equals cosine of this angle here. So I know that the sine of theta is equal to the cosine of 90 degrees minus theta. So I'm just going to replace this guy right here with this guy right here, right, since they're equal. So I'm going to say that this is the cosine of 90 degrees minus theta, and this is equal to this guy right here, which is the cosine of negative 55 degrees. Let me get rid of this scratch work here and get rid of that. And let me just slide this up here a little bit. And so what you would do here, you would set this guy equal to this guy, right? You set the angle measures equal. So we would say that 90 degrees minus theta is equal to negative 55 degrees. And so let me subtract 90 degrees away from each side of the equation. This would cancel. Slide down here just a little bit. We'll say the negative of theta is equal to negative 55 degrees minus 90 degrees. That's going to be negative 145 degrees. And then to finish this up, I'll divide both sides of the equation by -1. This would cancel. So you get theta is equal to, this will be 145 degrees. Now, again, this is not the only solution. Okay, again, when we get to solving trigonometric equations, we'll see that there's an infinite number of solutions. If you want, you can go back and plug this in, and you'll see that the sine of 145 degrees is exactly equal to the cosine of negative 55 degrees. Okay, now let's look at two examples where we're going to verify some identities. These are a little bit easier than what we looked at in the last section where we were strictly verifying identities. So let's start with, we have cosine of, we have theta plus pi, okay, is equal to the negative of the cosine of theta, okay. I'm going to flip this because the easier side is here on the right. So I'm going to write the negative of the cosine of theta is equal to the cosine of, you have your theta, okay, plus your pi. Now, what I'm going to do is just put my equals over here. I'm just going to slide this over for formatting, okay? Normally, they put it in line, but I just want a lot of room. So I'm going to expand this out using the sum identity for cosine. So this would be the cosine of theta, okay, times your cosine of pi. And then, remember, this is plus, so you want a minus. So I'm going to go the sine of theta times the sine of pi, okay? Now, realize when you work with the cosine of pi or the sine of pi, let's go back to the unit circle. When we look at pi over here, the cosine is -1, okay, and the sine is 0. So let's minimize this. So the cosine of pi is -1. So let's put times -1 like this. And the sine of pi is 0. Okay, so we know if you multiply anything by 0, it's going to be 0, right? So basically, you can get rid of this part right here, right? You'd have -0, which is just gone. So basically, I can say this is equal to the negative of the cosine of theta. And so that matches exactly what we have here, right? Negative cosine of theta, negative cosine of theta. So we're done. Okay, let's look at another example of verifying an identity. This one's just as easy. You have the cosine squared x minus the sine squared x equals cosine of 2x. Now, if it's not immediately obvious what you need to do, remember, if you have 2x, this is the same as x plus x. Okay, so if you're in this section, you're looking to think about the sum and difference identities for cosine. So think about things you can add or subtract. So 2x is x plus x. Okay, so what I'm going to do here, let's just go ahead and put equals here. I'm going to write cosine of x plus x like this, okay? And then I'm going to use my sum identity for cosine. So I'm going to say this is the cosine of x times the cosine of x again, then minus, remember this is plus, this is minus, the sine of x times the sine of x again, okay? So once you write it like this, it's clear that this is going to match, right? Because cosine of x times cosine of x, I can say this is the cosine squared of x, and then minus, I can say sine of x times sine of x is sine squared of x. And now I can see that this side matches this side, right? Cosine squared x minus sine squared x, cosine squared x minus sine squared x. So I can put my check mark there and I'm done. Okay, let's look at one more problem type that you're going to see. So we're asked to find the cosine of s plus t. You might also get the cosine of s minus t. The procedure, the way you do this type of problem is the same, okay? So you have s in quadrant 1 and t in quadrant 3. So they're giving you information about sine. So the sine of s is 3/5. The sine of t is -12/13. So the first thing we want to do is find the cosine of s, so that equals what? And the cosine of t, so that equals what? So one way you could do this is you could use your Pythagorean identity. Remember, cosine, in this case, let's say squared of s plus sine squared of s is equal to 1, okay? So if I plug in for sine of s right here, I can figure out what cosine of s is, okay? So let's scroll down. We'll come back up. So this is going to be 3/5. So remember, this guy is squared. So I'm going to plug in a 3/5 here, and I'm going to square that. So plus, you have your cosine squared of s, and this equals 1. Okay, so 3/5 squared is going to be 9/25. So this is 9/25. So plus, you have your cosine squared s here, and this equals 1. Okay, so I'm going to subtract that away from each side. So I'm going to have the cosine squared of s is going to be equal to, I'll go ahead and write 1 as 25/25. So I have a common denominator, and I'm going to subtract away 9/25, right? I'm just subtracting this away from each side. So 25 minus 9 is going to give me 16. And so I'll say I have cosine squared s is equal to, again, this is 16/25. If I want cosine by itself, I'm going to take the square root of this side. Again, you do plus or minus, but because we're in quadrant 1 for s, it tells us that I just want the principal square root of this guy, so I can erase this and just say I have cosine of s is equal to this. And so cosine of s will be the square root of 16 is 4, the square root of 25 is 5. So you get 4/5 there. So this guy is going to be 4/5. Okay, what about the cosine of t? Well, let's figure that out using the same process. Let's just change up this formula, and I'm going to put t here and t here. It's the same thing. I'm just going to plug in for this, so negative 12/13, but t is in quadrant 3 now, so keep that in mind. So let's come down here, and let's plug in. So we're going to have the cosine squared of t, then plus, and I hate using t because it gets confusing with this plus symbol. So let me use the plus symbol in like black or something so it's clear that this is a plus. I'll even circle it. That's a plus, okay? So then we have the sine squared t is equal to 1. I'm plugging in a negative 12/13 there, so negative 12/13, and this guy's being squared. So if I square a negative, I get a positive. If I square 12, I get 144. If I square 13, I get 169. So I'm going to say this is cosine squared t, and then let me be careful. I'm going to put the plus sign here. Okay, again, that's a plus. And then this is going to be 144 over 169, and then this is equal to 1. Okay, I'm going to subtract this away from each side. And before I do that, let me just get a common denominator going. So let's go cosine squared t. Okay, this is going to go over here. So I'm going to put equals, and I'm going to do 169 over 169, so that's 1. I just wrote it with a common denominator with this guy. Then minus, again, I'm subtracting this away from each side, 144 over 169, okay? So if I do 169 minus 144, I get 25. So let's scroll down just a little bit, and we'll say that cosine squared of t is equal to, again, this is going to be 25 over 169. Now, because we're going to be in quadrant 3, in terms of this t guy here, cosine is going to be negative. Okay, so I want the negative square root when I do this side. So I'm going to say cosine of t is equal to the negative of the square root of 25 over 169. So let's go ahead and simplify that. So we'll say the cosine of t is equal to, we'll have the square root of 25 is 5, the square root of 169 is 13. So the negative of 5 over 13. Okay, so that's going to be my cosine of t. Okay, so let's put negative 5 over 13 like this. So now that you have all the information, you can find cosine of s plus t. So sometimes they give you sine of one of them and cosine of the other. Sometimes they give you sine of one and then sine of the other. Just depending on the situation you're given, you want to just plug into the identities that you know about, come up with sine, cosine of each of the angles, and then you can go through and use your sum or difference identities depending on the problem. Here we're going to use the sum identity for cosine, and I'm just going to say that we have cosine of our s plus t is equal to, again, if I take my cosine of s, I know what that is. That's 4/5, then times my cosine of t, that's negative 5 over 13. This is a plus here, okay? So I want to make sure this is a minus. You're going to be really careful with the signs here because sometimes you'll make a mistake with that. So now I want the sine of s, which is 3/5, okay? And then I want times the sine of t, which is going to be negative 12/13, okay? So let's come down here a minute and just process this arithmetic. So I'm going to say this is equal to, if I multiply here, you see that this 5 would cancel with this 5, so basically I have a negative 1 there, okay? So this is basically negative 4 over 13, so negative 4 over 13, and then minus, you're subtracting away. This is 3 times negative 12, which is negative 36, I'm going to write this as, over 5 times 13, which is going to be 65. Now, I canceled here because we were doing multiplication, but it actually would have been smarter if I wouldn't have canceled, because then I'd have a common denominator. So let's undo this and say here we have 4 times negative 5, which is negative 20, okay, over 5 times 13, which is 65. In this particular case, it's better to not cancel because now I have a common denominator, and I can basically say what? I have negative 20 minus a negative 36. Again, you've got to be really careful with that sign. Negative 20 minus a negative 36, which is going to be negative 20 plus 36, which is 16. Okay, let me write this in a different color. So this is going to be 16, and then over, you're going to have 65. So this is going to be your answer for cosine of s plus t. In this lesson, we want to talk about the sum and difference identities for sine and also tangent. All right, so we talked about the sum and difference identities for cosine. Now we're just moving on and talking about the sum and difference identities for sine and tangent. just something you have to memorize. So if we have the sine of, let's say something like a plus b, again, don't distribute that and think it's sine of a plus sine of b. Okay, it doesn't work that way. You have to use this little formula here. So we're going to say this is the sine of a times the cosine of b plus the cosine of a times the sine of b. So notice how the sine here and the sine here is the same. Okay, and then when you get to this one, nothing's going to change except for the sign. So this is a minus and this is a minus. This part right here is the same. So the sine of, let's say, a minus b, now we're going to have the sine of a times the cosine of b minus the cosine of a times the sine of b. So with these, you just have to write them down and just go over it a few times in your mind, use it while you're doing the practice, and you're going to memorize it. Okay. So let's look at a little sample problem here. You saw this in the last section where we would basically rewrite something to get an exact value. You're going to do the same thing here. So we have sine of 165 degrees. So you're going to find two angles basically that are on the unit circle where you already know things about it. So I'm going to do the sine of, let's do 135 degrees. Plus, we're going to go 30 degrees, okay? So basically, if I use my little sum formula that I just talked about, this is going to end up being what? It's going to be the sine of the first guy, so 135 degrees, times the cosine of the second guy, which is the 30 degrees, then plus, it's the cosine of this first guy, the 135 degrees, and then lastly, times the sine of this last guy, the 30 degrees, okay? So some of you at this point are familiar with the unit circle, others are not. So let's just go really quickly so we can look at this guy just in case you need to pause the video and get the values. When you're looking at 30 degrees, your cosine is going to be square root of 3 over 2. Your sine is going to be 1/2, okay? And then when you look at 135 degrees, your cosine is going to be the negative of the square root of 2 over 2, and your sine is going to be the square root of 2 over 2. So let's come back up and just punch these values in, and we'll basically be done. So I'm going to put equals here, and then basically the sine of 135 degrees is the square root of 2 over 2. So I'm going to say this is the square root of 2 over 2, times, for the cosine of 30 degrees, I've got the square root of 3 over 2, then plus, for the cosine of 135 degrees, I've got the negative of the square root of 2 over 2, and then lastly for the sine of 30 degrees, I've got 1/2. Okay, so now all we have left to do here is just basically go through and do some basic operations. So we're going to multiply here. So basically square root of 2 times square root of 3, really all I can do is say that's the square root of 6 over 2 times 2, which is 4. Then plus, if I do the negative of the square root of 2 times 1, it's just the negative of the square root of 2. So really I could just change this to minus, okay? And I'll put the square root of 2 over here over 2 times 2 is 4, okay? So basically in this type of situation, generally speaking, you're going to write this with a common denominator. So I'm just going to come down here, get some room going, and I'll just say that this is the square root of 6 minus the square root of 2 all over the common denominator of 4. Okay, so this is the exact value of the sine of 165 degrees. All right, so another type of problem you'll see is something where you're asked to simplify. And basically, you just need to realize here that you can use the difference identity for sine. It's kind of going in reverse here. But basically, to solve this problem and to simplify. So if you notice here, you have sine of 3 theta times cosine of negative 2 theta minus the cosine of 3 theta times the sine of negative 2 theta. Okay, so if you notice here, this angle right here and this guy right here, it's the same. You have the sine of this guy and the cosine of this guy, and you have a minus, okay? Then if you look at this guy, it's negative 2 theta and negative 2 theta, cosine of this guy, sine of this guy. So this matches our little formula here. The sine of A times the cosine of B minus the cosine of A times the sine of B. So in other words, you see sine of 3 times theta, and then you see the cosine of 3 times theta over here. And then here, you've got this cosine of negative 2 times theta, okay? And then here, you've got this sine of negative 2 times theta, okay? So basically, what you're going to do is realize that it's this angle right here minus this angle right here. So it's 3 times theta minus a negative 2 times theta, which is going to give us 5 times theta, okay? So that's what that's going to work out to. So I'll just put equals here. I'm just going to put the sine of, I'm going to take this first angle here, this 3 times theta, minus a negative, okay, you have your 2 times theta, okay, that guy right there. And so this would give me, again, if I just combine this, 3 times theta, basically minus a negative is plus a positive, so you would have sine of 5 times theta. All right, additionally, you have the sum and difference identities for tangent. So let's start with the sum guy. So we have the tangent of, let's say, a plus b. This is going to give us, we have the tangent of a plus the tangent of b over 1 minus the tangent of a times the tangent of b. And what's going to happen when we change over to this difference guy, the signs here are just changed. So before, when this was plus and this was minus, okay? Now that this is minus and this is plus. So again, just something you have to write down and just keep practicing with, and you will commit it to memory. All right, let's take a look at an example with this guy. So suppose you're given the tangent of pi over 12. So if you want to find the exact value, again, one way you can do this is by using these sum and difference identities. So I like to work with degrees when I do this. It's just easier versus me trying to figure out what I need to add and subtract using fractions. So if you can do this with fractions, just skip this step that I'm about to do. But I'm going to convert this first into degrees, and then you can go back to radians, okay? So I'm going to go pi over 12 times, I'm going to go 180 degrees over pi. And then basically, this would cancel with this and give me 15 degrees, okay? This is going to cancel out. So pi over 12 in terms of radians is the same as 15 degrees. Okay, so now that I got this in terms of degrees, what two angles could I add or subtract to get 15 degrees? Well, one thing you could do is 45 degrees minus 30 degrees, okay? So I could write this as the tangent of 45 degrees in terms of radians is going to be pi over 4, okay? And then minus, if I think about 30 degrees in terms of radians, it's going to be pi over 6. Okay, so pi over 6. All right. So the next thing I want to do before I even use my formula, I know I'm going to need the tangent of pi over 4. So I know I need the tangent of pi over 4. And I know I need the tangent of pi over 6. Let's go back to the unit circle. I know some of you have this memorized, some don't. So let's just go back to the unit circle. So if we're looking at our pi over 4, or 45 degrees, we have square root of 2 over 2 and square root of 2 over 2. So that means the cosine and the sine are the same. And basically, the tangent is the sine divided by the cosine. And since it's the same number, right, the same number divided by itself is going to give you 1. Okay, so we know that, and I'll just write this down. The tangent of pi over 4 is just going to be 1, okay, because you have square root of 2 over 2 divided by square root of 2 over 2, so that gives you 1. Then the tangent, if I think about for pi over 6, this is going to be what? Well, you want the sine, which is 1/2, divided by the cosine, which is the square root of 3 over 2. So basically, I would flip this guy, okay, because I'm dividing fractions. So let's put the 2 up here and the square root of 3 over here, okay? And then basically, the 2's cancel, and I have 1 over the square root of 3. So 1 over the square root of 3. Of course, we're going to rationalize this. So I'm going to multiply this by the square root of 3 over the square root of 3. And so this is going to give me the square root of 3 over 3. Okay, so let me write this in a more compact way. So square root of 3 over 3. Let's copy this, okay? And let's go back, and let's just paste this in here real quick. And so this is 1, and this is square root of 3 over 3. Okay, so square root of 3 over 3. Okay, so now that we figured that out, we can use our little difference identity. And for this guy right here, let me put equals. It's going to be, and I'm just going to slide this off to the side for 1 second. So this is going to be the tangent of the first guy. So the tangent of pi over 4 is going to be 1. So it's going to be 1, then minus the tangent of the second guy. So minus the tangent of pi over 6, which is the square root of 3 over 3. Then this is over. Remember, you have your 1. The sign is different here, so it's going to be plus. You're going to multiply them together, right? So the tangent of pi over 4 times the tangent of pi over 6. So basically 1 times this guy. So it would be plus the square root of 3 over 3. Okay, so let's get rid of this. We don't need it anymore. Now, basically, you have a lot of different options here when it comes to simplifying, okay? I am going to choose to basically multiply the numerator and denominator of this guy by 3, okay? So this is going to get distributed here and here. This is going to get distributed here and here. So what is this going to give me? Let me scroll down and get some room going. So 3 times 1 is obviously 3. And then minus, this would cancel with this, and I'd have the square root of 3 there, okay? So we'll put this over here, and I'll kind of undo this real quick, just showing that. Over here, 3 times 1 is 3, then plus, again, the 3's would cancel there, and you'd have the square root of 3. Okay, so now this is a little bit simpler, but really, in order to go anywhere, what I'm going to do, remember, if you have a radical down here, you have this plus here, if this is binomial like this, then basically what you can do is you can multiply by the conjugate. okay? So I can wrap this and I can wrap this. So I'm going to multiply this by, I'm going to have 3 minus, okay, I'm changing the sign from plus to minus, then the square root of 3, okay? Then over, you would have 3 minus the square root of 3. Again, this is just a complex form of 1. When you multiply these guys together, you're just going to do the first guy squared minus the last guy squared. Remember, the middle two guys are going to drop out. Okay, so let me make sure I got my equal sign going. So put that in there. Let's keep going. All right, so in the top, realize this is 3 minus square root of 3 quantity squared. So I can use a formula on that. Take the first guy and square it, so 3 squared. And then this is minus, so minus, it's 2 times the first guy, which is 3, times the last guy, which is square root of 3, and then plus the last guy, square root of 3 squared is 3, okay? You can simplify this right now. 3 squared is 9. Then basically 2 times 3, you know that's 6, so you'd have minus 6 times the square root of 3, and then plus 3. Now, 9 plus 3 is 12, so let me just go ahead and put this as 12 minus 6 times the square root of 3, okay? So we have that, and I can even shorten this a little bit and put this like this. Now down here, all I need to do is square the first guy, so 3 squared is 9, and then subtract away, if I square this guy, square root of 3 squared is just 3. Now I can just perform this operation. 9 minus 3 is just 6, okay? Now we're not done, because notice that you have 12 here, which is divisible by 6, 6 here, which is divisible by 6, and 6 here, okay? So what I'm going to do is I'm just going to factor a 6 out from the numerator. So this is going to be 2 minus the square root of 3, okay, over 6 down here. And now we're done, right? We cancel this, and I end up with 2 minus the square root of 3 as my answer for the tangent of pi over 12. All right, let's look at an example where we're going to verify an identity. So we have the cosine of beta is equal to the sine of, we have this pi over 6 plus beta, and then plus we have cosine of, we have pi over 3 plus beta. Okay, so basically we always want to work on the more complex side. Obviously the right side is way more complex. So I'm just going to put equals over here. Okay, and normally we line this up, but I want to give myself lots of room. So basically what I'm going to do is I'm going to use my sum identity here and my sum identity here. Okay, so I'm going to first say that I have the sine of this pi over 6 times the cosine of this beta, okay? Then plus, okay, so now I'm going to do the cosine of this guy right here. So let me change color. So I'm going to go the cosine of this, in this case, pi over 6, and then times you have your sine of beta. So your sine of beta. Now, additionally, I want to do the same thing with this cosine guy. So I'm going to put plus here. Remember how to do this. I'm going to go cosine of this guy. So cosine of pi over 3, and then times the cosine of the next guy, so cosine of this beta here. And then if this is plus, it's going to go minus, right? So the signs are going to be different there. And then now I'm going to do the sine of this guy, sine of pi over 3, times the sine of beta. Okay, so now what we want to do is think about what can we replace? Well, think about the fact that you have the sine of pi over 6 and the cosine of pi over 6. So coming back to my unit circle, again, when we think about pi over 6, the sine is a half and the cosine is square root of 3 over 2. So let's just write this down. So we had the sine of pi over 6 is 1/2. And we had the cosine of pi over 6. That's going to be the square root of 3 over 2. Now, additionally, we were also working with this pi over 3, right? So we need the sine and cosine for that guy as well, okay? So the cosine for pi over 3 is going to be 1/2. And the sine for pi over 3 is going to be the square root of 3 over 2. Okay, so let's go ahead and grab this guy, and we're going to cut it away. And I'm just going to come down here real quick and paste this in so we have it. So let's just replace the sine of pi over 6 with 1/2 and the cosine of pi over 6 with square root of 3 over 2. Okay, so let's come up here. So let's go ahead and put equals. Instead of the sine of pi over 6, I'm going to put 1/2 and then times my cosine of beta, okay? Plus, for this guy right here, I'm going to put the square root of 3 over 2. So the square root of 3 over 2 times my sine of beta, okay? And so let's get rid of these two right here. We don't need them anymore. And let me scroll down a little bit, and I'll drag these up into our visual range, okay, so we can work with them. Let's come back up here real quick. So now we want to replace this cosine of pi over 3. So I'm going to put plus. This guy is going to be 1/2. And then times your cosine of beta. Okay, so let's get rid of this. And then lastly, I'm going to put this minus here. We have the sine of pi over 3, which is the square root of 3 over 2, So let's get rid of this. And this is times our sine of beta. Okay. And sometimes I put multiplication signs and sometimes I don't. You don't need it. Sometimes I just put it there. Okay. So let's scroll down a little bit, get a little bit more room going. Let's think about what we can do. So we'll notice here that this guy right here, okay, and this guy right here, those can be canceled, right? You have the square root of 3 over 2 times the sine of beta, and then you have the negative of that. So I can just cross that out. Those are gone. So basically I can say this is 1/2 times cosine of beta plus 1/2 times cosine of beta. So let's stop for a second. Remember what we're trying to get. We're trying to just get the cosine of beta. So basically, if you have a half of something plus another half of something, you have one of that thing. You basically have a common denominator here, right? You could say this is the cosine of beta plus the cosine of beta over 2, right? And you have 2 of this. So let's go ahead and come down here and just say that we have basically 2 times the cosine of beta over 2. And we can cancel that. And lastly, we will say that we have the cosine of beta, okay? And so we've verified our identity. All right, let's look at one other type of problem here. We're going to be asked to find the sine of theta plus beta, the tangent of theta plus beta, and the quadrant of theta plus beta. So a very common type of problem. Unfortunately, they do take a while to work out. So let's go ahead and come down here. And for this one, I'd like for you to try it on your own before we even go. We did a similar problem with cosine in the last lesson. So we have sine of theta is equal to 4/5. We have the cosine of beta, which is equal to the negative of 5/13. And then we're told that theta is in quadrant 2 and beta is in quadrant 3. Okay, so how do we figure this out? Well, what we need is the cosine of theta. So that equals what? Okay, that equals what? And we need the sine of beta. So that equals what? Okay, if we have these two pieces of information, then we can use our little formulas that we've been talking about in the lesson. Okay, so basically, how do we get this? If we know the sine of theta is 4/5, well, I can start off by saying, well, the sine squared theta plus the cosine squared theta equals 1. Okay, remember your Pythagorean identity. So I can plug in here a 4/5, and that's going to be squared, right? So 4/5, and this is going to be squared. So this ends up being 16 over 25 plus the cosine squared theta is equal to 1. Again, I'm just going to move this over here. So let me scroll down a little bit. I'm just going to say that I have cosine squared theta is equal to, if I subtract this away from each side, I'd have 1 minus 16 over 25. If I make this as 25 over 25, then basically 25 minus 16 is 9, so you would have 9/25, okay? But now the issue is I want cosine of theta, not cosine squared theta. So basically I need to square root each side. Remember, you get plus or minus over here, and then based on what quadrant you're in, that's how you decide what sign you're going to use. Now we're told that theta is in quadrant 2, okay? And in quadrant 2, cosine is negative. So I'm going to go cosine of theta is equal to, I'm going to use the negative of the square root of 9 over 25. And of course, this is going to end up giving me the cosine of theta is equal to negative square root of 9 is 3, and then the square root of 25 is 5. So negative 3/5, okay? So let's take this up. So we're just going to cut this away. And actually, I'll just write it in here. So I'll put negative 3/5. So that's the first piece of the puzzle. So now we need to find the sine of beta. I'm going to use the same thought process. So the cosine of beta is the negative of 5/13. So again, we have the sine squared, in this case beta, plus cosine squared beta is equal to 1. And for cosine squared beta, remember for cosine itself, I'm plugging in a negative 5/13, and this guy's being squared. Don't forget to square. Okay, so if I square this guy, I'm going to get 25 over 169. So I'm going to have sine squared beta plus this guy here equals 1. Same thing, I'm just going to move it to the other side. So I'm going to say sine squared beta is equal to, let me go ahead and put this as a common denominator. So 169 over 169, same thing as 1. Then minus this guy over here, I'm just moving to the other side. So minus your 25 over 169. And so the sine squared of beta is equal to 169 minus 25 is 144. So you have 144 over 169. Now, we said that beta was in quadrant 3, and in quadrant 3, sine is going to be negative. So I'm going to say the sine of beta is equal to the negative of the square root of this guy, so the 144 over 169. So the square root of 144 is 12, the square root of 169 is 13. So I'll go ahead and say the sine of beta is equal to the negative of 12/13. thirteenths, okay? So the negative of 12 thirteenths. So let's put this up here, the negative of 12 thirteenths. Okay, so we are officially ready to answer this part up here, the sine of theta plus beta, okay? So basically, you would have the sine of theta plus beta is equal to the sine of theta, which is 4/5, multiplied by the cosine of beta, which is negative 5/13, okay? Then plus, you have your cosine of theta, which is negative 3/5, and then times your sine of beta, which is negative 12/13, okay? I'm going to wrap this in parentheses so I don't make a silly sign mistake. Now, in a lot of cases, you'll notice when you're multiplying here, you can cross cancel. Here, notice that you have 5 times 13 and 5 times 13. So don't cancel this because you're going to want to have a common denominator. I make that mistake all the time, so I'm just going to stop you from doing it. Okay. So basically, 4 times negative 5 is negative 20. And this is over. 5 times 13 is 65. Then plus, negative times negative is positive. So 3 times 12 is 36. Over 5 times 13 is again 65. Okay. So to finish this up, I'd have negative 20 plus 36, which is 16, and then over the common denominator of 65. So sine of theta plus beta is 16 over 65. So let's just erase all this work. So sine of theta plus beta is equal to 16 over 65. Okay, so how do we get the tangent of theta plus beta? Well, first, I need the tangent of theta, and I also need the tangent of beta. So how do I get that? Remember, for the tangent, you divide the sine by the cosine. So if I think about, let me go down here because we're going to forget stuff. So if I want the tangent of theta, it's going to be the sine of theta, which is 4/5. So 4/5 divided by the cosine of theta, which is negative 3/5. Again, we're dividing fractions. So flip this guy. I'm going to multiply by the reciprocal. So times 5/3. This cancels and I get negative 4/3. Okay. So let me just scooch this down. So this is going to be negative 4/3, okay? And then we want the tangent of beta. So how do we get that? Same way. So I'm going to do negative 12/13. Let me change my ink here. And then times, over here, I'm going to flip this. So I'm going to do negative 13/5. And again, stuff's going to cancel. So this cancels with this. Negative cancels with negative. That's positive. So you have 12/5, right? So this is positive 12/5. Okay. So let me drag this back up. So let's cut this away. And let's paste this in here, okay? And let's see if we can figure out what the tangent of theta plus beta is. Again, I take the tangent of the first guy. Let me write this off to the side. So the tangent of theta plus beta, okay? So the tangent of the first guy, which is negative 4/3, then plus the tangent of the second guy, which is 12/5. This is over. We want 1, again, this is plus because it's the same as this. This is going to be minus, right? So this is always different. This is always the same. So 1 minus, multiply the 2 together. So it's negative 4/3 times your 12/5, okay? And let me get rid of this now. We don't need it just so we have some room. So let's move this over. Let's move this over. Okay, put this over here. And I'm going to drag this up here a little bit. And I'm just going to scroll down a little bit. We'll come back up in a second. So the best way to do this, let me just put equals over here. I'm not going to get a common denominator yet. So I'm going to go negative 4/3 plus 12/5 over. For this one, I'm just going to multiply. Negative 4 times 12 is going to be negative 48. And this is over. 3 times 5 is 15. And you've got 1 minus this, okay? So what is the LCD if I think about all the fractions involved? If I think about 3, and that's a terrible 3, so let me make that better. So if I think about this 3 here, let me get off the marker mode. So this guy, the 3, the 5, and the 15. Well, it's 15, right? So the quickest way to do this, in my opinion, is to multiply the top and bottom by 15, okay? So I'll save you a lot of time. We'll go ahead and distribute this here, and then here, and here, okay? So first off, minus a negative is the same as plus a positive, okay? You can just change that right away, so you have to deal with it. And you'd have 15 divided by 3 is 5. 5 times negative 4 is going to be negative 20. Then 15 divided by 5 is 3. 3 times 12 is going to be 36. So plus 36. You can go ahead and do that if you want. You know that's going to be 16. So this is 16. This is over. If you multiply 15 by 1, that's 15. And then 15 divided by 15 is 1. So you just have plus 48 there. So what's 15 plus 48? It's going to be 63. Okay, so this guy's going to be 16 over 63. And I could put equals there. But really, I'm just going to erase all of this. And I'll just put a little line here, put the tangent of theta plus beta is equal to, and let me just paste that in, my 16 over 63. Okay, so sine of theta plus beta is 16 over 65. Tangent of theta plus beta is 16 over 63. Now we want to think about, and I can just get rid of this, we want to think about the quadrant of theta plus beta. Well, I just want you to think about the sine. The sine of theta plus beta is positive, right? So sine is positive, okay? The tangent of theta plus beta is also positive. So the tangent is also positive, okay? So where is sine positive and also tangent positive? Remember, you can always draw your little coordinate plane, and I know this is a terrible freehand draw, but it's all students take calculus, right? You have your sine, your tangent, and your cosine, okay? So if we think about sine, it's positive in quadrants 1 and 2, and tangent is positive in quadrants 1 and 3. So the only guy that meets both criteria here is going to be quadrant 1, okay? So the quadrant of theta plus beta, okay, is going to be 1. So this is going to be, we'll say, is in quadrant, I just probably put a capital Q, so quadrant 1. In this lesson, we want to talk about the double angle, the product to sum, and also the sum to product identities. All right, so at this point, we've learned quite a few of the trigonometric identities. We just keep adding on to the ones that we already know. I'm just going to pop open this little worksheet here real quick. So this is the whole worksheet. If you go back up to the top, this is all the stuff we've already learned. So all of these guys we've already talked about. And now we're getting into the double angle identities. And then again, we'll talk about the product to sum and the sum to product at the end of the video. But right now, we're going to focus on these. So you can either pause the video and write these down really quickly, or you can use the worksheet that's been provided. Okay, so the problem we're going to look at here is just going to be asking to find some trigonometric function values. We have the cosine of theta is equal to 2 times square root of 2 over 3. And we have that sine of theta is greater than 0, or you could just say positive, right? So basically, if it's cosine of theta is positive and sine of theta is positive, that tells me that we're in quadrant 1, right? So we can say here that theta is in quadrant 1. So we're going to need that piece of information. Now, what we're going to be asked to find is the cosine of 2 times theta. So we want to find the cosine of 2 times theta. We also want to find the sine of 2 times theta, okay? And then also we want to find the tangent of 2 times theta. And of course, once you have these, you can use your reciprocal identities to find the other ones. I'm just going to do these 3 right here. All right, so the first thing I'm going to do, what I'm going to focus on is finding the sine of theta and the tangent of theta, okay? And then we're going to use our identities to find the cosine of 2 times theta, the sine of 2 times theta, and the tangent of 2 times theta. Okay, so if I'm given cosine of theta, how can I find sine of theta? Again, we've done this a million times. One way we can do this, we can say that cosine squared theta plus our sine squared theta is equal to 1. Okay, so our Pythagorean identity, something we're really used to working with at this point. So for this guy, I'm going to plug in this 2 times square root of 2 over 3. And I'm just going to square this guy. Okay, let me just copy this and go to a fresh sheet because we're going to run out of room here. So let's come down here and just paste this in so we have lots of room. And then I'm just going to say plus my sine squared theta is equal to 1. Okay, so from here, if I squared 2, I would get 4. If I squared the square root of 2, that's 2. Okay, and if I squared 3, I would get 9. So basically 4 times 2 is 8. So this is 8/9. Then plus your sine squared theta is equal to 1. I'm just kind of drag this up here. And from here, I'm just going to say that I have sine squared theta is equal to, I'm going to subtract 8/9 away from each side of the equation. So I'm going to put 1 minus 8/9. Okay, and again, all I did was subtract it from both sides of the equation. And so now what I have is my sine squared theta is equal to, if I write this as 9 over 9, so I have a common denominator, and then I'm subtracting away this 8/9 here, this on the right-hand side is going to be 1/9. So I would say sine squared theta, okay, is equal to 1/9. Okay, now from here, in order to get rid of this kind of squaring operation, I'm going to take the square root of each side. Normally, again, you do the plus or minus on the right-hand side, but because we're in quadrant 1, I know that sine is positive, so I want the principal square root. So I'm just going to say that the sine of theta here is going to be the principal square root. Let me show this fully. So the principal square root of 1/9, Okay, so the sine of theta is equal to square root of 1 is 1, square root of 9 is 3. Okay, so let me just write this up here that the sine of theta, so the sine of theta is equal to 1/3. Okay, and we'll come back up and we'll use this. Let's come back down here for a second. Let me erase all of this. So I'm also going to need my tangent of theta. So the tangent of theta, we all know that this is the sine of theta divided by the cosine of theta. So the sine of theta we just found was 1/3, okay? And the cosine of theta, if I go back up here, it's 2 times square root of 2 over 3, okay? But because I'm going to be dividing fractions, I'm going to go ahead and flip that guy and multiply. So this is 3 over 2 times square root of 2, okay? So what's going to happen is the 3's are going to cancel, and I have 1 over 2 times the square root of 2. I want to rationalize the denominator here, so I'm going to multiply by the square root of 2 over the square root of 2, okay? So basically, if I think about what I'm going to have here, in the numerator, it's just the square root of 2. In the denominator, it's 2 times the square root of 2 times the square root of 2. Square root of 2 times square root of 2 is 2, so 2 times 2 would be 4, okay? So the tangent of theta is the square root of 2 over 4. So let's just write this here, that the tangent of theta is the square root of 2 over 4. Okay, so now let's go ahead and find the cosine of 2 times theta, the sine of 2 times theta, and the tangent of 2 times theta. So for the cosine of 2 times theta, let's go back to our little sheet here. So we have cosine of 2a. You could plug in theta for a or x or whatever you want to do. It's cosine squared of a minus sine squared of a. So that's pretty easy to do. So let's make a little border here. And actually, I'll probably be better off just going to the other sheet. So we'll say cosine of 2 times theta is going to be equal to cosine squared theta minus sine squared theta. Okay, so I'm just going to plug in. So cosine of 2 times theta is equal to, remember our cosine of theta was 2 times the square root of 2 over 3. Okay, this guy's going to be squared. Then minus, remember our sine squared theta, you might remember this was 1/9, but basically sine of theta was 1/3. Right, so I'm going to put 1/3 here and square it, and that's going to give me 1/9. Okay, so if you remember from earlier, when we squared this, we got 8/9, right? Because 2 squared is 4. Square root of 2 squared is 2. 4 times 2 is 8, okay? And basically 3 squared is 9. So this is 8/9 minus, let me put equals over here. I'll just write the whole thing out. So cosine of 2 theta is equal to 8/9 minus, again, if you square this, you get 1/9, okay? So this gives me a final result here of 7/9. So this is my cosine of 2 theta. Okay, so let's come up here and put that our cosine of 2 theta is equal to 7/9. Now, if you're asked for the secant of theta, you would just flip that and get 9/7. Okay, but we're not asked for that here. So then now I want to find the sine of 2 theta. Okay, so what's this going to be equal to? Let's come back down here. So what is my sine of 2 theta? Well, let's go back to our worksheet here, and we see that the sine of 2a is equal to 2 times the sine of a times the cosine of a. So again, you could just plug in. You could say the sine of 2 times theta is equal to 2 times the sine of theta times the cosine of theta. So this is equal to 2 times the sine of theta times the cosine of theta. Well, again, we know the sine of theta is 1/3. So this is 1/3. And we know the cosine of theta is 2 times the square root of 2 over 3. So let me put my 2 in here, and let me put sine of 2 theta like this. So let me write this again over here. Let me put sine of 2 times theta is equal to, basically I'm just going to multiply across. 2 times 1 times 2 is going to be 4, then times the square root of 2 over 3 times 3 is 9. Okay, so sine of 2 theta is equal to 4 times square root of 2 over 9. So let me just move this down a little bit. Or actually, I can put it over here. So the sine of 2 times theta is equal to 4 times the square root of 2 over our 9. And again, you could flip this to find the cosecant of 2 theta, okay? But again, you'd have to rationalize the denominator there. We're not asked for that here, so we're not going to do that. Okay, so lastly, we want the tangent of 2 theta. So how do we find this? Well, essentially, all I need to do is take this guy right here and divide it by this guy right here, or I can use my formula. So let's see this both ways. So for the tangent of 2 times theta, the first way we're going to do it, probably the easier way, you basically take your sine of 2 times theta, which again is 4 times square root of 2 over 9. So 4 times square root of 2 over 9. We're going to multiply it by the reciprocal of this cosine of 2 theta, which is 7/9. So if you flip that, you get 9/7. Again, I'm flipping that because if you're dividing fractions, you take the first fraction, multiply by the reciprocal of the second. So this is going to cancel. We're going to be left with 4 times square root of 2 over 7. So that's the quickest way. That's the way you probably want to do this. So let's come back up here. So 4 times square root of 2 over 7. Now the other way, and I just want to show you this with the identities. It's a little bit longer, but I think you should see it. Let's pop this open. We have the tangent of 2a is equal to 2 times the tangent of a over 1 minus tangent squared of a. Okay, so let's come down here and say that the tangent of 2 times theta is equal to 2 times the tangent of theta over 1 minus tangent squared theta. Okay, so what is the tangent of theta? If we go back up, the tangent of theta was square root of 2 over 4. So let's come back over here. And I'm just going to put this over here. So the tangent of theta was the square root of 2 over 4. So we would start with, and let me just put equals over here, 2 times this guy right here, which is square root of 2 over 4, okay, over 1 minus tangent squared theta. So I'm just going to square this guy. So if I square, let me just show this. So if I square the square root of 2, I'm going to get 2. If I square 4, I get 16. Okay, so I'm going to go ahead and say this is multiply across. I'll say this is 2 times square root of 2 over 4 over, you would have 1 minus, again, if I square square root of 2, I get 2. If I square 4, I get 16. Okay, let me scroll down and get a little bit of room going here so we can see what's going on. It's probably quicker for me to just multiply this by 16 over 16. That will cancel all my denominators. So 16 times this guy, the 16 would cancel with the 4 and give me a 4. So you'd have 4 times 2, which is 8. So let me put 8 times the square root of 2 here. And then down here, 16 times 1 is 16. And then minus 16 times this guy right here. The 16s would cancel, so I just have 2. Okay, so that's probably a quicker way versus what I was going to do, which is basically to work with these guys individually. Okay, so now 16 minus 2 is going to be 14. So this is 8 times square root of 2 over 14. Okay, and basically I can cancel this 8 and this 14. They're each divisible by 2. So this is going to be 4 and this is going to be 7. Right, so we get 4 times square root of 2 over 7. And you see that's what we got before, right? So it's much quicker if you have the sine of 2 times theta and the cosine of 2 times theta to just work with that versus using the formula. But sometimes you're told to show it on a test or something like that. So if you do it the alternative way using the double angle identity, it works the same. All right, so now we're going to look at a similar problem, but it's going to go in reverse. So now we're given the cosine of 2 times theta. In this case, it's equal to the negative of 7 over 25. We're told that theta is in quadrant 4. Now, you might be thinking that the cosine of theta should be positive in quadrant 4. But remember, this is the cosine of 2 times theta. Okay, so not the cosine of theta. This is the cosine of 2 times theta. So what we're going to find here is the 6 trigonometric functions, those values for theta. Okay, so basically, I would start off by finding my sine of theta. I can then use that to find the cosine of theta. And from those two guys, I can basically find all the rest, right? Really easy to do. So how am I going to find the sine of theta given this information? Let's go back to our little worksheet, or you could say handout. And basically, if you look here, you have this guy right here, which would work pretty nicely. You have the cosine of 2a is equal to 1 minus 2 times sine squared of a. So let's use that. So we have the cosine. Let me do this on another sheet. So we have the cosine of 2 times, in this case, I think it was theta. So it was theta is going to be equal to 1 minus 2 times sine squared theta. Okay. Now I know what cosine of 2 times theta is, right? I'm given that as negative 7 over 25. So just plug in for that. So we're going to say this is negative 7 over 25, okay, is equal to 1 minus 2 times sine squared theta. All right, so from here, let's go down a little bit and get some room going. I'm going to basically flip this around. I want what I'm solving for on the left. So I'm going to add 2 times sine squared theta to both sides. So I would have 2 times sine squared theta, okay, is equal to, I'm going to leave this guy over here, and I'm going to add 7/25 to both sides. So basically, I'm going to have 7 over 25 plus 1 over here, okay? So all I did was just kind of swap things around. It's just adding and subtracting the same thing to both sides of an equation, which is legal, okay? So basically, what I want to do at this point is go ahead and add 7/25 plus 1. So I'm just going to write this as 25 over 25. And this would give me 32 over 25, okay? So I would have over here 2 times sine squared theta is equal to 32 over 25. I have this 2 that I want to get rid of, so I can multiply both sides by a half. So let's multiply this side by a half and this side by a half. And basically, this is going to cancel out. And over here, this would cancel with this and give me 16. Okay, so now let me keep scrolling down here. We have that sine squared theta is equal to, you have 16 over 25. Okay, so you have to take the square root of each side. Again, if we go back up, we are told that theta is in quadrant 4. We know that the sine of theta, if it's in quadrant 4, is going to be negative, right? Because sine is positive in quadrants 1 and 2. So if we come back here, what I want to do is take the negative square root of this right-hand side. So I'm going to say the sine of theta is equal to, I'll go the negative of the square root of 16 over 25. So the sine of theta is equal to the negative of, square root of 16 is 4, square root of 25 is 5. So sine of theta here is equal to the negative of 4/5. Okay, so let's go back up and let's put right here, the sine of theta is equal to negative 4/5. All right, so how do we find the cosine of theta and all the rest of them? Well, basically at this point, we can just use our regular identities that we've been working with. I can use the Pythagorean identity to get this guy. So we know that sine squared theta plus cosine squared theta equals 1. So I'm going to have my negative 4/5 for my sine of theta. I'm going to square that plus my cosine squared theta. This equals 1. Okay, so if we square this, we get our 16 over 25. Then plus our cosine squared theta. This equals 1. Let's subtract this away from both sides. So I'm going to have cosine squared theta is equal to, I'm just going to write this as 25 over 25 to speed this up. And over here, I'm going to put minus. Again, I'm subtracting this away from each side. So 16 over 25. Okay, so from here, it's pretty easy. We have cosine squared theta is equal to 25 minus 16 is 9. So this is 9 over 25. Okay, so we're in quadrant 4. Cosine is going to be positive in quadrant 4, okay? So what I want to do is take the principal square root of this right-hand side. So I'm going to say the cosine of theta is equal to the principal square root of 9 over 25. So now let's finish this up and say the cosine of theta is equal to, square root of 9 is 3, square root of 25 is 5. So this is 3/5. So let's come back up, and this will be 3/5, okay? So then the tangent of theta is found by what? You basically take this guy right here, this negative 4/5, and you multiply by the reciprocal of this 5/3, okay? And this cancels, and you get negative 4/3. So this is negative 4/3. And then the other guys are found with the reciprocal identities. So let's just go ahead and do the cotangent really quickly. So the cotangent of theta, that's found by flipping this, so it's negative 3/4. Then if I want, let me scroll down just a little bit. If I want the cosecant of theta, that's found by flipping this sine of theta. So this is negative 5/4. And then lastly, if I want the secant of theta, that's found by flipping the cosine of theta. So that's going to be 5/3. Okay, let's look at two examples of verifying some trigonometric identities. You always want to get practice doing this because it keeps coming up again and again and again. And the more you work on it, the better you're going to be when you need it for calculus. Okay, so we have the cotangent of x times the quantity 1 minus the cosine of 2x is equal to sine of 2x. So the first thing I'm going to do is flip this. I'm going to put sine of 2x here basically on the left-hand side for formatting. And I'm going to put is equal to, let's just go ahead and put cotangent of x times the quantity 1 minus the cosine of 2x. Okay, so how can we approach this problem? The first thing I always like to do, if I see something like the cotangent of x or the tangent of x, the first thing I'll try to put things in terms of sine and cosine. It doesn't always work that way, but in this case, it will work out this way. So we have the sine of 2x is equal to, I'm going to go ahead and say that the cotangent of x is the cosine of x over the sine of x. And this is times the quantity 1 minus the cosine of 2x. Now, you have 1 minus something, and I want you to look at the identities here. If you go back here, notice you have this 1 minus 2 times sine squared of a here for the cosine of 2a. Okay, so if I plug this in here, I can get that 1 to drop out. So I'm going to go ahead and write this as the quantity, make sure you use parentheses here, 1 minus 2 times sine squared, in this case, of x. Okay, so you need parentheses there because you're subtracting the whole thing away. And what I'm going to have here, let me put my equals over here. And I know normally you line this up, but I want a lot of room, so I got to do it over here. So cosine of x over sine of x times, in this case, you could go ahead and write this as 1 minus 1 plus 2 times sine squared x. And see how the 1s are going to cancel out there? So let's scroll down a little bit more. get some room. I'm going to say is equal to, I'm going to go cosine of x over sine of x times 1 minus 1 is 0, right? So that's gone. You have 2 times sine squared x. Now you can do some canceling, right? This is going to go away. I can get rid of one of these, right? So basically, what I can do here is say that I have 2 times sine of x times the cosine of x. Now let's stop for a minute. If we go back up, we're trying to get the sine of 2x. Okay, so that's what we want. So is there an identity that matches that? If we go back, we have that the sine of 2a is equal to 2 times sine of a times cosine of a. So we're basically done, right? We can basically replace this right here with the sine of 2x. So we can go ahead and put a big fat check mark there to show that we're done. Okay, let's look at another example. Again, I just want to do a lot of examples of these. So we have 1 plus the cosine of 2x is equal to the cotangent of x times the sine of 2x. Okay, so which side is more simple? I would say that because this has cotangent involved and this just has cosine, right? This is cotangent and sine over here and you have cosine. So I would not mess with the left-hand side. I would mess with the right-hand side. So I would put equals over here and I would change this into, again, cosine of x over sine of x just to get started. Again, it doesn't always work out that way. And then you have the sine of 2x. So be careful here. Don't go through and cancel this with this immediately because this is not like having sine squared of x, right? This is sine of 2x. So you basically want to use your little formula where the sine of 2 times x is basically 2 times the sine of x times the cosine of x. So let's put cosine of x over sine of x. And let's say basically over here we have, instead of sine of 2x, I'm going to put times 2 times the sine of x times the cosine of x, okay? So now we can cancel this with this. Again, don't cancel it here. That's not correct. You have to cancel it here when it's sine of x and sine of x, or if you had sine squared of x or something like that, then you can cancel. But sine of 2x, you're not going to be able to cancel with sine of x. It doesn't work that way. So let's come down here a little bit, okay? And let's go ahead and put our equal sign. And now basically what I'm going to have is 2 times cosine squared of x. So you might think you have a little stopping point here because I'm trying to get 1 plus cosine of 2x. But again, if you look at your identities, you're going to find something that can match. So if I come back here, right now we have 2 times cosine squared of x, okay? If I add 1 to each side, it's exactly what I'm looking for, right? Cosine of 2a plus 1 is equal to 2 times cosine squared of a, okay? So basically I'm just going to replace this guy right here with its alternative form. I'm going to say this is equal to 1 plus the cosine of 2x. Okay, so straight from your identities handout, we'll go ahead and put a check mark there because we're done. Okay, let's look at some problems that involve the product to sum identities and also the sum to product identities. These come in a variety of forms. Sometimes you're asked to find the exact value. Sometimes you're asked to simplify. These guys are really easy to work with, as long as your teacher allows you to have the sheet in front of you. Otherwise, you do have to memorize them, okay? So what we have here is 2 times sine of 105 degrees times cosine of 75 degrees. So basically this is a product, okay? And we're going to want to change this into a sum to get an exact value. So let's go to our little worksheet here. And there's quite a few of these. So let's go to basically where we have our sine of a times our cosine of b like this. This is going to be 1/2 times, inside these brackets here, you have the sine of a plus b plus the sine of a minus b, okay? So let's just put this down here, and I'll just write it out really quickly for you. So basically, if we have the sine of a times the cosine of b, okay, which is what we have right here, then basically this is going to be 1/2 times the sine of, let me put this in brackets, a plus b, okay? And then you have your plus your sine of, let me slide this down, this is not going to fit. So your sine of your a minus b, okay? So let's close that down. So the first thing is you can cancel this immediately by saying you have 2 times this 1/2 here, or you can cancel it later. It doesn't really matter. You can put this as 2 times, and then you can put brackets here, and then put 1/2, and then put more brackets, and then put your sine of, what's a in this case? That's going to be 105 degrees. What's b? That's 75 degrees. So 105 degrees plus 75 degrees is 80 degrees, okay? And let me just write this like this. I'll just put sine of 80 degrees plus the sine of, what's a minus b? What's 105 degrees minus 75 degrees? That's going to be 30 degrees, okay? So you can put these brackets here. Again, it's not going to matter because when 2 gets multiplied by 1/2, it's basically going to be 1. right? So it's basically gone. So we can just say that we have the sine, and I put 80 degrees. This should be 180 degrees. So the sine of 180 degrees plus the sine of 30 degrees. So at this point, you should be very familiar with your unit circle. The sine of 30 degrees you should know is 1/2, and the sine of 180 degrees you should know is 0. So this basically turns into 0 plus 1/2, which gives me 1/2, okay? So just a little formula where you start off with something that looks kind of hard to work with, you plug some things into the formula, and you get an exact value of 1/2. Okay, let's look at an example of what we call a sum to product. Here we're just going to be asked to simplify. So you have the cosine of 13 theta minus the cosine of 5 theta, okay? So basically we want to change this into a product. So let's go ahead and go back and look at now. If we come down here, we have the sum to product identities. We have the half angle identities, but we'll get to that in the next lesson. So what we have here is cosine of sum A minus cosine of sum B. This equals -2 times the sine of this A plus B over 2 times the sine of this A minus B over 2. Okay, so let's go back and let's just write this down here. So basically the cosine of A, okay, minus the cosine of B is equal to -2 times the sine of, you have this A plus B over 2, okay, times the sine of, you have this A minus B over 2, okay? So I'm just going to plug in. A is going to be 13 theta, and B is going to be 5 theta, okay? So let's think about this. I'm going to put equals, and I'm going to carry this over here, and let's just go ahead and say that we have -2 times the sine of, what's A plus B? Well, it's 13 theta plus 5 theta, so that's going to be 18 theta over 2, okay? So I can go ahead and reduce that and say that's basically 9 times theta, right? So sine of 9 times theta, and then basically you could say times the sine of, so the sine of, we have A minus B now, so 13 theta minus 5 theta is going to be 8 theta, okay, over 2. Again, 8 divided by 2 is just 4, so you can put that like that. That's basically all we can do if we're asked to write this as a product. So we have -2 times the sine of 9 theta times the sine of 4 theta. In this lesson, we want to talk about the half angle identities. All right, so we're going to wrap up our section now on the trigonometric identities and get ourselves prepared for solving trigonometric equations. But before we do that, we need to talk about these half angle identities. So let me quickly go back to our handout. So we have all of our trigonometric identities listed here. So these are the ones we've already talked about. Let me just keep scrolling down here. We're going to come down to all the way down where we have these half angle identities, okay? So you see you have ones for cosine, sine, you have 3 for tangent. Again, something you need to basically memorize if you want to go quickly through these problems, but in a lot of cases, they're going to let you have these handouts, so it's something you could just refer to back and forth, okay? So I'm going to come back to these when I need them. The first one I'm going to need is this guy, so you can pause the video and write it down, or you can have your handout, whatever you want to do. But the cosine of some angle A over 2 is equal to plus or minus the square root of 1 plus the cosine of A over 2. Now this plus or minus here is there to tell you that you want to take the appropriate sign based on the quadrant that you're in. Remember, cosine is going to be positive in quadrants 1 and 4. Okay, so let's go ahead and minimize this. Let's go to the first problem here, where we're told to find the cosine of 67.5 degrees. Now, before I start, let me just put this off to the side. Let me put my identity here. So the cosine of, let's say, A over 2 is equal to, we have plus or minus, you have the square root of, you're going to do 1 plus the cosine of this A over, you're going to have 2. Okay, so let me just slide this down just a little bit. So this is what we're going to be using here. So basically, if I want to write this angle here as some angle over 2, I would first multiply it by 2 to figure that out, right? So 67.5 times 2 is going to give me 135, right? So I would say this is equal to the cosine of 135 degrees over 2, okay? So now this guy right here matches my format right here, okay? So I can use my little identity here. So let's just put equals here. And I'm going to put, since we're trying to find the cosine of 67.5 degrees, remember, it has nothing to do with this guy that's being divided by 2. This is what we want here, okay? So this angle right here is going to be in quadrant 1. So we know cosine is positive in quadrant 1. So we want to use the principal square root. So I'm going to say this is equal to the principal square root of 1 plus the cosine of, here's where it gets tricky. This is A, this is A. Okay, so you want the cosine of 135 degrees and then over 2. Okay, so this is what we're going to be figuring out. Now, hopefully at this point you've memorized the unit circle, but if you haven't, I have it here. So basically, if you go to 135 degrees and you look at your x coordinate here, this is going to be the cosine of 135 degrees. So you have negative of the square root of 2 over 2. And all we need to do is replace that here. Okay, and once you have that, it's basically just a lot of simplifying. Okay, so let's just put the square root of 1 plus, again, this is the negative of the square root of 2 over 2, and then all over 2. And I should probably make this a little bit bigger so it encompasses the whole thing. Let's continue this over here. So the quickest way to do this, in my opinion, you could get a common denominator there, but I'm just going to multiply by 2 over 2. Okay, so 2 times 1 over here would be 2. Let me make my square root symbol. And then 2 times you'd have negative square root of 2 over 2. The 2's would cancel. So you're basically subtracting away the square root of 2. So I'm going to put minus the square root of 2. And this is over. 2 times 2 here is 4. Okay, so we can quickly simplify this by realizing, again, you could write this as the square root of 2 minus the square root of 2 over the square root of 4. And we know the square root of 4 is 2. Okay, so I can come down here. Let's finish this up and just put this is equal to the square root of 2 minus the square root of 2. You can't really do anything else there. Over the square root of 4 is 2. Okay, so that's going to be your exact value if you're looking for the cosine of 67.5 degrees. All right, let's take a look at a similar problem. Now we're going to have the tangent. So we have the tangent of 7 pi over 12. And for this one, again, if you get radians, if you're really good at working with fractions, you can do it in this way. I always just convert these into degrees because it's just easier for me. Okay, so I'm going to first say we have 7 pi over 12 times, again, to convert this, you want to put pi in the denominator, and you want to put 180 degrees in the numerator. Always remember that 180 degrees equals pi radians, okay? So this is your unit fraction. It's basically equal to 1, and we can use this to cancel. So this cancels with this, and 180 divided by 12 is 15, okay? So you can just cancel this out and put 15. 15 times 7 is 105. Okay, so this will end up giving me 105 degrees. So let's erase this real quick. And I'm just going to put that this is equal to the tangent of 105 degrees. And then I'm just going to double this number, okay, because I'm going to use this half angle formula. So I'm going to say this is equal to the tangent down here of 105 degrees times 2 is 210. So 210 degrees over 2. Okay, so which formula do we want to use? Let's go back to our worksheet. So you have several here to choose from. You can pick this one right here. I think it's probably the easiest. The tangent of a over 2, there's no square root symbol to work with. It's the sine of a, so the sine of whatever this is up here, over 1 plus the cosine of a. So let's go ahead and write this maybe off to the side. We have that the tangent of a over 2 is equal to, again, this is the sine of a over, you have 1 plus the cosine of a. So what do I want to do here? Again, this is going to be what I'm plugging in for a here and here and here, okay? So basically I would say this is the sine of 210 degrees over, you have 1 plus the cosine of 210 degrees, okay? So we don't need this anymore. I'm just going to erase it for room, okay? And then I'll just put equals here. What is the sine of 210 degrees? Let's go back to our little unit circle. So you have the sine of 210 degrees is negative 1/2, and you have the cosine of 210 degrees is negative square root of 3 over 2. So let's now plug in. So the sine of 210 degrees is negative 1/2, and then this is over. Let me scroll down and get a little bit of room here. So again, this is over 1 plus, what's the cosine of 210 degrees? It's the negative of the square root of 3 over 2. So let me put minus here instead of plus. So the negative of the square root of 3 over 2. Okay, so now all we really have to do is simplify this guy. Pretty easy overall. I'm just going to multiply the top and bottom by 2. So this gives me what? This is going to cancel, right? The 2's would cancel, and I just have negative 1 up here. And then this is over. Down here, 2 times 1 is 2, and then minus 2 times this guy right here. The 2's would cancel, and you would just have the square root of 3. Okay, now you don't want to leave this way because you don't ever want a radical in the denominator. So you need to rationalize the denominator. So let's put equals over here, and I'll put negative 1 over 2 minus the square root of 3. okay? Remember how to rationalize this. When this guy is basically two terms, you want to use the conjugate, right? So the terms would be the same. The 2 would be the same and the square root of 3 would be the same, but you're going to choose the alternate sign, okay? And the reason for this is when you go through and do the FOIL down here, you're going to have those middle two terms drop out, so you're just going to have the first guy squared minus the second guy squared, okay? So let's go ahead and put equals here. In the numerator, we know what this is going to be. It's just going to make everything negative. So it would be, let's say, -2, then minus the square root of 3. Down here, you would have the first guy squared, so 2 squared is 4. And then minus the last guy squared, which would be 3. Well, 4 minus 3 is 1. So basically, anything over 1 is just itself. So I can just say the answer here is -2 minus the square root of 3. All right, let's take a look at another common problem for this section. So your book will probably say something like finding function values of s over 2 given information about s, okay? So in this particular case, we are given that the sine of theta is 4/5, and theta is basically in quadrant 2, right? Because it's greater than 90 degrees and less than 180 degrees. So you can basically say that theta is in quadrant 2. Okay, so we have that information. Now, what if I asked you to find, let's say, the sine of theta over 2, and then let's say we want the cosine of theta over 2, and also the tangent of theta over 2. And of course, you can get the other ones with the reciprocal identities. We're just going to do these 3 because basically, once you have those, you can get the other ones easily, okay? So first and foremost, where is theta over 2? So theta over 2 is in what quadrant? So this is very confusing for a lot of people, but basically to determine this, you would just divide everything here by 2, okay? Because that would give you theta over 2. Now, 90 degrees divided by 2 is 45 degrees, okay? So that would be less than theta over 2, which is also less than 180 degrees divided by 2 would be 90 degrees, okay? So this tells me that theta over 2 is greater than 45 degrees and less than 90 degrees, so it's got to be in quadrant 1. So it's in quadrant 1. So keep this in mind when you're working with these guys because you've got to choose the appropriate sign, okay, for your trigonometric functions. Now, if we go back to our identities, you'll see to find cosine of a over 2 or sine of a over 2, you need to have the cosine of a, okay, in each case. So that means we first need to find cosine. So let me go to a fresh sheet. We know that the sine of theta is 4/5, and we know that from the Pythagorean identities, we can say that 4/5, which is basically sine squared theta, plus cosine squared theta is equal to 1, okay? So what I can do here is just go through and find cosine of theta. So basically, we've done this a million times. We know if we square 4, we get 16. If we square 5, we get 25, okay? Plus cosine squared theta is equal to 1. I'm going to subtract this away from each side of the equation. So this is going to be my cosine squared theta is equal to, this will be -16 over 25, and then plus 1, okay? So let's come over here. I know that I need a common denominator now, right? So you can just erase this right now and just put 25 over 25. So 25 minus 16 is 9. So I'm going to say cosine squared theta is equal to 9 over 25. So this is where a lot of students struggle. I'm going to put the cosine of theta is equal to plus or minus the square root of 9 over 25. Now, which sign should I choose? Let's go back up, and let's remember that we're working with theta for right now, not theta over 2, okay? So this is where people get confused. They make a sign mistake. So it's theta. Theta is in quadrant 2, okay? If I'm in quadrant 2, cosine is negative, okay? So that means that in this particular case, I want to choose the negative square root, okay? So I want to say the cosine of theta is equal to the negative of the square root of 9 over 25. So the cosine of theta here is equal to -3 over 5, or you could say -3/5. So let's go back up. So let me write this in here. The cosine of theta is going to be equal to -3/5. Okay, so now we have that piece of information. And I want to find the sine of theta over 2, the cosine of theta over 2, and the tangent of theta over 2. Again, we know that theta over 2 is in quadrant 1, so all of these guys, if there's a square root involved, you want the principal square root, okay? So if I go back to my little sheet, we have the sine of a over 2 is equal to, again, we just want the principal one, the square root of 1 minus the cosine of a over 2. So let me first write this out. So we would have the principal square root of 1 minus the cosine of, in this case, this is your a, right? You got to substitute this. This is theta. This will be theta here. And then this will be over 2, okay? So cosine of theta we know is negative 3/5, so I'm just going to plug that in. So minus a negative is plus a positive, so I'm going to put plus 3/5. Now, how you go about doing this, let me make this better. So 3/5 like this. How you go about simplifying this is up to you. Of course, you could write 1 as 5/5 and then basically add your fractions. Or you could multiply this here by 10/10. It's whatever you want to do, whatever's quicker. Let's just do it this way. So I'm going to say 10 times 1 is 10, okay? And then 10 divided by 5 is 2. 2 times 3 is 6. So 10 basically plus 6 would be 16. So let's say this is 16 over 10 times 2 is 20, okay? So I'd have the square root of this guy. Let me kind of slide this down a little bit. I'm kind of working with some narrow space here. So let's come down here, and let's put this is equal to, of course, 16 and 20 are both divisible by 4. So divide 16 by 4, you get 4. Divide 20 by 4, you get 5, right? So what is the square root of 4/5? Well, the square root of 4 is 2, and then over the square root of 5. Now, I need to rationalize the denominator, so I'm going to multiply this by the square root of 5 over the square root of 5. And so this gives me 2 times the square root of 5 over 5, okay? So all that, just to get this answer here of 2 times the square root of 5 over 5, okay? Now for the cosine of theta over 2, we have a similar formula. We come back here. Again, we're using the principal square root. It's 1 plus the cosine of, in this case, it's theta. Here it's a, but in our case, it's theta over 2. So let's come back and say this would be what? The square root of, you have the 1 plus, what's the cosine of theta? Well, it's negative 3/5. So in this case, you don't have the minus and negative. It's straight up minus 3/5. And then this is over 2, okay? Let me make this a little bit better and make this longer like this. And let's come down here. So let's say 1 minus 3/5. Let's do this an alternative way. Let's just say this is 5/5, okay? So 5 minus 3 would be 2. So basically you would have the square root of, you would have 2/5. If you're dividing by 2, you can just multiply by half. So what you'd have here is the 2's cancel. And so you'd have the square root of 1/5. So let's erase all of this and put the square root, and I made that terribly, so the square root of 1/5. And of course, the square root of 1 is 1, so 1 over the square root of 5. You need to rationalize the denominator, so this is times the square root of 5 over the square root of 5. And so this becomes the square root of 5 over 5, okay? Let's erase all this, and let's slide this all the way down, okay? So this is going to be right there. So square root of 5 over 5, and that's probably too tight. So square root of 5 over 5. Okay, so for the tangent of theta over 2, again, you can come back here and use one of these guys. But again, remember, you can just use your definition of the tangent, okay? So I can just divide this guy by this guy. So I can basically say 2 times the square root of 5 over 5. If I'm dividing with fractions, I just multiply by the reciprocal. So I'm going to flip this, and I'm basically going to have 5 over the square root of 5. And so we see that this would cancel, okay? This would cancel, and I just get 2, okay? So the tangent here is going to be 2. So now we've found all of the guys that we were looking for. So if we're looking for the sine of theta over 2, it's 2 times square root of 5 over 5. The cosine of theta over 2 is square root of 5 over 5. And the tangent of theta over 2 is just going to be 2, okay? So again, if you wanted to find the other ones, you could flip this guy right here in order to find your cosecant of theta over 2. Flip this guy right here in order to find your secant of theta over 2. And flip this guy right here to find your cotangent of theta over 2. All right, let's look at one more problem here, and this just involves verifying an identity. It's just important to get a lot of practice with this, not only for calculus, but because in this section in trigonometry, it just keeps coming up over and over and over again, and there's no general set of rules to follow for this. It's all just practice, right? So manipulating things, trying to make sure it works out, and then just keep going. As long as you're making proper algebraic substitutions, you will eventually get where you want to go, okay? So if I look at this, I have 1 plus the sine of beta is equal to this quantity, sine of beta over 2 plus cosine of beta over 2 squared. Okay, so obviously the left side here is much simpler. So I'm just going to work on the right side. Normally you put your equal sign in line here, but I'm going to have to move this all the way over here just because I'm going to run out of room, okay? The first thing I'm going to do, you remember if you have something like x plus y quantity squared, this is the first guy squared plus 2 times the first guy times the second guy plus the last guy squared, okay? So I'm just going to do that here just to expand this guy out. So I'm just going to say that we have basically the sine squared of this beta over 2 plus 2 times this guy times this guy. So this sine of beta over 2 and then times cosine of beta over 2 and then plus the last guy squared. So cosine squared of this beta over 2. Okay, so from here, you want to think about, if I look at this guy, what do I have here that I can maybe do something with? So nothing really with the half angle identities. You actually have to go all the way back up to the Pythagorean identities. Remember, we used this earlier. The sine squared theta plus the cosine squared theta equals 1. Okay, so if we think about this, we have sine squared of beta over 2, so this is just some angle, plus cosine squared of that same angle, beta over 2. So this plus this would be 1. Okay, so I can just basically say that that's 1 plus your 2 times sine of beta over 2 times the cosine of beta over 2. And let me get rid of this marking here because I'm kind of in the way. And from here, you're really thinking about now your double angle identities from the last section, okay? Remember what you're trying to get to. If you look at this, you have 1 plus the sine of beta. So for this guy right here, we have the sine of 2a is equal to 2 times the sine of a times the cosine of a, okay? So this is what I have here, right? I have 2 times the sine of beta over 2 times the cosine of beta over 2. So I'm going to go and write it like this, sine of 2 times beta over 2, okay? So I want to put this as 1 plus, we'll say, the sine of 2 times beta over 2. The 2's are going to cancel, and look at what I have. I have 1 plus the sine of beta, okay? And if I go back up, I'm looking for 1 plus the sine of beta, so bam, we got it. And I know these things are kind of hard. I've obviously already worked the problem, so I know what to do. But when you're working with these, don't get frustrated. Again, you can always try to put things in terms of sine or cosine, perform any factoring, perform any squaring, and just get as much practice with these as you can, because when you get to the test, you have to get them done in a reasonable amount of time. In this lesson, we want to talk about inverse trigonometric functions. All right, so before we get into the inverse trigonometric functions, I want to recap some things that we talked about earlier in the course. It's going to be really important that you understand this information in order to fully understand this lesson. So first and foremost, we discussed the idea of a one-to-one function. So in a one-to-one function, each x value corresponds to exactly one y value. And additionally, you could say in a one-to-one function, each y value corresponds to exactly one x value. So often you'll hear for each x there's one y, and then for each y there's one x. Now, when you have a one-to-one function, you can verify that using something called the horizontal line test. So for the horizontal line test, if you have the graph of a one-to-one function, no horizontal line will impact that graph in more than one location. So a common source of confusion when you work with inverses would be the notation that's involved. So I have here, if a function f is a one-to-one function, then the inverse of f is denoted as, here this is f inverse. So again, this is the inverse of my function f. Now, this right here is what you have to get straight. This is not an exponent of -1. That is a very common source of confusion. Later on in this lesson, when we get to inverse trigonometric functions, you'll see something like y is equal to the inverse sine of x, and that's one way to write it. We have a different way to write, and I'll get to that later on. But you need to know that this is not an exponent of -1. This is telling me I have the inverse sine of x. Now, provided that your function, let's just call it f of x, is a one-to-one function, you're going to be able to find the inverse using this little procedure. So to find the f inverse of x from f of x, again, f of x is a one-to-one function here, we're going to replace f of x with y. We're going to swap x and y. Then you're going to solve for y. And then once you've done that, you're going to replace y with f inverse of x. So this right here, this swapping x and y, this leads to the following. So we have that the domain of f, so the domain, remember, as the set of allowable x values, will become the range of f inverse. So the range is the set of allowable y values. So again, the x's and the y's were switching places. So that's what's causing this. The domain of f or the x values, will become the range of f inverse, or the y values. So the x's and the y's are switching places. Similarly, the range of f will become the domain of f inverse. Again, the x's and the y's are switching places. So this tells us if a comma b is on the graph of f, then b comma a is on the graph of f inverse. So notice that these guys switched roles. So here, this is your x, and then here it becomes your y. And then here, this is your y, and then here it becomes your x. So again, the domain of f becomes the range for f inverse, and the range of f becomes the domain for f inverse. So your x's become the y's, and the y's become the x's. Very important. And then I have here the graphs of f and f inverse are reflections across the line y equals x. So there are many cases where we're going to have a function that's not a one-to-one function, but we still want to find the inverse. So in that situation, what can we do? Well, let's start off with something that we did earlier in the course. We looked at the squaring function. So this graph right here is for f of x is equal to x squared. So clearly this is not a one-to-one function. Let's just use the horizontal line test real quick to prove that. So this would be the line y is equal to 4. Now if you look at this horizontal line, it is impacting this graph of f of x equals x squared in two locations. So right here and then right here. So again, if you have the graph of a one-to-one function, no horizontal line will impact that graph in more than one location. So this right here will not be a one-to-one function. If you look at this point right here, from the origin, we're going 2 units to the left and 4 units up. So this is negative 2, 4. If I look at this point right here, from the origin, I'm going 2 units to the right and 4 units up. So this is going to be 2, 4. So the issue is that this y value of 4 is associated with two different x values, here with negative 2 and here with positive 2. And that's coming from that squaring operation. If I plug in a 2 for x, 2 squared is 4. If I plug in a negative 2 for x, negative 2 squared is also 4. So when this happens, what can we do? Well, like we saw earlier in the course, we can impose a little domain restriction. So for this graph right here, we start with f of x equals x squared. So that's the squaring function. But you would notice that it seems like I've cut off anything to the left of 0. So basically, we would say that x here is greater than or equal to 0. So this is going to create a one-to-one function, and this is the key. The range is going to be the same. So we're going to see that's going to be important as we get into these trigonometric functions and the inverse trigonometric functions that we create from restricting the domain. So the range here is the same. Before it was from 0 to positive infinity, and now it's still from 0 to positive infinity. Now let's just prove that real quick. I'll just put in this same horizontal line here. So again, this is y is equal to 4. And notice that now, when I draw this line, it's going to impact the graph only in one location. And that's true for any horizontal line that you would draw here. So this is now the point 2, 4. My point, negative 2, 4, that was on the other one, where I didn't restrict the domain, that's gone because x can't be negative 2 here. X can only be 0 or anything larger. So I only get 2, 4. So basically, in the inverse, I'm going to have 4, 2. Right, so 2, 4, and then 4, 2. So for each x, there's one y, and now for each y, there's going to be one x, so I'll be able to find an inverse. Okay, so let's just go through that real quick. Hopefully you know how to do this from earlier in the course. If not, let's just go through it once, so that later on it'll be easy. So basically, you start off by replacing f of x with y. So let me write here that we're going to find the inverse. And you would start by replacing, again, f of x with y, so y equals x squared. Then the next step is to swap x and y. So we're going to say that we have x is equal to y squared. So this y became x, this x became y. That's all you're doing. Then your next step, you're going to basically solve for y. So first I would write this as y squared equals x. As my personal preference goes, I like what I'm solving for to be on the left. And then I would use the square root property. So you would say that y is equal to plus or minus the square root of x. So here's where we have to pause and think. In this function right here that's domain restricted, f of x equals x squared, we said that x is greater than or equal to 0. Well, we know that the domain from this function right here becomes the range for the inverse. So specifically here, I would say that y is greater than or equal to 0. So I don't need this plus or minus here because I can't have the negative of the square root of x because I'm specifically saying that y is greater than or equal to 0. So I'm going to get rid of this plus or minus and say that y is going to be the principal square root of x. So let me replace this with y is equal to the principal square root of x, and I'll get rid of this. And then step 4 is just to replace your y with your f inverse of x, and so this is equal to the square root of x. All right, so before we move on, it might be helpful to look at this graphically. This is especially useful when you're trying to figure out if you got the right inverse. Remember that a function and its inverse are going to be reflections across the line y equals x. So you can always look at this graphically and see that. So this graph right here, for this guy in orange, this is our f of x equals x squared, where we said that x is greater than or equal to 0. If you're going to do this on Desmos, you want to do this as f of x equals x squared, and then you're going to open up some brackets and you're going to put in your restriction. So x is greater than or equal to 0, and then just close those and it'll give you this graph here in orange. Okay, then the graph in red, this is just the line y is equal to x, or you could put f of x equals x, whatever you want to do. And the graph in blue, this is our inverse. So f inverse of x is the square root of x. I'm just going to put this as g of x. So f of x and g of x, those are going to be inverses, and this is equal to just the square root of x. Now, what you can do is look at a few points and just prove a few things. So first off, let's just start with this point right here. So this point right here, I'm going 3 units to the right and 9 units up from the origin. So this is going to be the point. Let me arrow to this. So this would be 3, 9. Now again, if I reflect this across the line, y equals x, I'm going to get this point right here. So this point right here would be 9, 3. So notice that the x value, which was 3, is going to become the y value here. And the y value here, which is 9, is going to become the x value here. So the x's and the y's are switched. Then let's just do one more. So this point right here, if you look at it, is going to be 2, 4. So this point right here is 2, 4. And then if you look at, again, reflecting across the line y equals x, you're going to get this point right here. And now, instead of 2, 4, you're going to get 4, 2. So this is always something you can use if you're trying to figure out if you got the right inverse. It's very helpful to graph your function, graph your inverse, and graph the line y equals x. And just look at if your function and the inverse are reflections across the line y equals x, then you know you got the right one. All right, now let's move on and talk about how to find the inverse trigonometric functions. We're going to start off with how to find the inverse sine function. And so to do that, we're going to begin with our graph of f of x equals the sine of x, or we could say y is equal to the sine of x. So we studied this graph earlier in the course. At this point, you should know that the domain is a set of real numbers and the range is from -1 to +1. So let me write this out. So the domain is going to be the set of real numbers. So from -infinity to +infinity. So that means I can plug in any real number I want for x here. So a negative, 0, positive. As long as it's a real number, I'm good to go. Then in terms of the range, we can see that's from -1 to +1. And you should know that from the unit circle. So let's go ahead and put from -1 to +1. Clearly, this guy is not the graph of a one-to-one function. If I draw a little horizontal line like this, well, you can see that I'm going to hit here, and here, and here, and here, and here, and here, and here. And remember, this continues forever to the right and forever to the left. So I'm going to keep hitting over and over and over again. So obviously, this is not the graph of a one-to-one function. It fails the horizontal line test. So what can we do when we encounter this situation? Again, just like with the squaring function, we restricted the domain such that we had the same range. So let me actually erase this and show you what we're going to do. We're going to take a piece of this graph. So we're going to go from right here, this is -pi/2, to right here, this is pi/2. Let me write that a little bit more neatly. So again, this is -pi/2 here. So you're going to take right here to right here. So just a piece of that graph right there. And now it's going to pass the horizontal line test. So it'll be a one-to-one function. It'll have the same range from -1 to +1. So let me come to this graph here. It's a little bit easier to see things. So this is called the restricted sine function. So basically it's your sine function with a restricted domain. So we have y is equal to your sine of x. And then we would say that x is greater than or equal to -pi/2. And then less than or equal to pi/2. So obviously the domain is from -pi/2 to pi/2 with those guys included. Let me just write this out. So the domain is going to be from -pi/2 to pi over 2, with both of those guys being included. And this is the key here. The range is the same. So if you go back to the y equals sine of x, again, the range is from -1 to +1. Well, here, even though we've restricted the domain, the range remains from -1 to +1. So let me write that the range is going to still be from -1 to +1. Okay, so now let's cover the inverse sine function. So we're going to start with the restricted sine function. So that's going to be this graph in orange. Let me just trace over what the computer drew here. So this is my graph in orange. A lot of stuff is overlapping here, so it's pretty hard to see it clearly. But this graph, again, is y is equal to my sine of x, where x is greater than or equal to -pi over 2 and less than or equal to pi over 2. So that's the restricted sine function. If you reflect it across the line, y equals x, you're going to generate this graph here in green. So let me go over that. So from here to here. So a lot of overlap here. You can do this on Desmos if you want a cleaner picture. But in terms of the video, I think it's going to come through at least good enough to where you can see what's going on. So this right here is going to be the graph of the inverse sine function. Typically, you'd write that as y is equal to the inverse sine of x, like that. You could also write this as y is equal to the arc sine of x. Although if you're in a trigonometry course, this is typically more common, but some books use this. It just depends. So you need to know both of those in case you run into one and not the other. Okay, so basically, like we saw earlier, you're just taking this point right here, which is from the restricted sine function, and you're reflecting it across the line, y equals x, to get this point right here on your inverse sine function. So notice that this x value of pi over 2 becomes the y value of pi over 2 here in the inverse, and the y value of 1 becomes the x value of 1 in the inverse. We can also take this point right here, and again, reflect it across the line y equals x to get this point right here. So you see this x value of -pi over 2 becomes the y value of -pi over 2, and then the y value of -1 becomes the x value of -1. Okay, so let's look at a cleaner graph here. So this is the graph of y is equal to your inverse sine of x. And you can see that the domain of this guy came from the range of your restricted sine function. Let me actually put a little border here. And let me write y is equal to the sine of x. And let me put that x is greater than or equal to -pi over 2 and less than or equal to pi over 2. And let's consider that the domain of this guy, so the domain of this guy, is the same as the range from this guy. So the domain here is from -1 to +1. So this is going to be from -1 to +1. Well, here, if you look at the range, it's from -1 to +1. Then if we think about the range for this guy, so the range, this is coming from the domain of the restricted sine function. So it's going to be from -pi over 2 to pi over 2. So from -pi over 2 to pi over 2. And then the domain here, of course, we know this at this point, but let's just write it one more time. So again, this is from -pi over 2 to pi over 2. So just like we talked about, the domain from the restricted sine function becomes the range in the inverse. And then the range in the restricted sine function becomes the domain and the inverse. So the x's become the y's and the y's become the x's. All right, now let's look at a few sample problems. So we're going to start with y equals the inverse sine of 1/2. So we just want to figure out what is the value for y here. So if you were to key this into your calculator, so if you were to type in the inverse sine of 1/2, you would get pi over 6 if you're working with radians, or you would get 30 degrees if you had it set to degree mode. So why does it give you that answer? So why does it give you pi over 6 and not the 5 pi over 6 that you would see on the unit circle? So we can see that for pi over 6, I have a sine value of 1/2, but then also for 5 pi over 6, I have a sine value of 1/2 as well. Well, what's going on? Well, to see this, let's think about deriving the inverse algebraically. We saw a graphical representation of it, but now let's do it algebraically, and we'll get a little bit more insight into what's going on. So let's say you start with, again, y equals the sine of x. And of course, we need to make this 1-to-1 so we can have an inverse. So x is greater than or equal to -pi over 2 and less than or equal to pi over 2. So to find the inverse, if you had f of x, you change it to y. Well, that's already done for us here. And then basically you'd swap x and y. So this y becomes x and is equal to the sine of this x becomes y. Okay, well now this domain is going to become the range. So this is y is greater than or equal to -pi over 2 and less than or equal to pi over 2. Now, this is a form that you're going to see in your textbook. What they'll say is from here, in order to solve it for y, we're just going to say that it's y is equal to the inverse sine of x. So this right here is just solved for y. It means the same thing as this. Now, I'm going to concentrate on it in this form for right now. It's a little bit easier to think about it. So basically, let's say that we start with this right here. So the domain restricted sine function. We know that a point on that graph is going to be pi over 6, comma, 1/2. So where did I get that from? Well, first off, pi over 6 is within the domain. It's greater than or equal to negative pi over 2 and less than or equal to pi over 2. So if I plug that in for x, I get a true statement. So it's within the domain. And the sine of pi over 6 is 1/2. So this would be a point on the graph. Well, when I get to the inverse, these are switched. So now this is 1/2, comma, pi over 6. In other words, when I look at this guy, I am asking the question, let's say I plugged in a 1/2 here for x. I'm saying, what angle in the interval from negative pi over 2 to pi over 2 is going to have a sine value of 1/2? If we go to the unit circle, I'm going to look at this right here. So this is what I'm looking for right here. So this is pi over 2, and then this down here, if you're rotating clockwise, this is going to be negative pi over 2. So this is what you're looking for here. If your argument is positive, like we have here, we're going to be looking at things in quadrant 1. If your argument is negative, you're going to be looking at things in quadrant 4. Now, there's an exception to what I just said. If you have the inverse sine, so if you have the inverse sine of 1, that's going to give you pi over 2. And of course, that's a quadrantal angle. If you had something like the inverse sine of 0, that's going to give you 0. So 0 is not a positive number, but if you plug that in, you're going to get something that's a quadrantal angle. And then also the inverse sine of, let's say, negative 1, that's going to be negative pi over 2, and that's coterminal with 3 pi over 2. So again, these are quadrantal angles, but if I say something like the inverse sine function is going to give you something in quadrant 1 if the argument is positive, and quadrant 4 if the argument is negative, you need to just know these exceptions. Let me get rid of this real quick, and let's go back to what we were talking about. So here we have the inverse sine, so y equals the inverse sine of 1/2, or we wrote this as x is equal to the sine of y, where specifically y is greater than or equal to negative pi over 2 and less than or equal to pi over 2. So again, where in this interval am I going to have a sine value of 1/2? Well, again, this argument is positive, so I'm only going to look in the first quadrant, and I see that I have a sine value here of 1/2, and that is going to be right here at pi over 6. So that's why I'm getting this pi over 6, and I'm not getting this 5 pi over 6 here as an answer. If you notice, you have a sine value of 1/2 for 5 pi over 6. And a lot of students will always complain, well, why am I not getting the 5 pi over 6? You're not getting it because it's not within the range of the inverse sine function. So to answer this, if you have y equals the inverse sine of 1/2, let's just write the inverse sine of 1/2 is going to be equal to pi over 6. All right, let's look at y equals the inverse sine of a negative square root of 2 over 2. So this one's a little bit more tricky. Let's come down to the unit circle. Let me write y is equal to the inverse sine of negative square root of 2 over 2. Again, you can stick with it in this form if you want. You're just looking in quadrant 4 for an angle whose sine value is going to be negative square root of 2 over 2. That's what you're looking for. You can again write it as the sine of y is equal to x, where y is greater than or equal to negative pi over 2 and less than or equal to pi over 2. And of course, you could just plug in a negative square root of 2 over 2. So again, y is the angle in this interval where we have a sine value of negative square root of 2 over 2. Now, because this is negative, I want to work in quadrant 4. Let me just highlight the whole thing first. Let me highlight the whole thing first so we get comfortable with this. And basically, if I go into quadrant 4 and I'm looking for a sine value of negative square root of 2 over 2, it's going to be right there. So this is going to be at 7 pi over 4. Now, is 7 pi over 4 the answer? No. You cannot say that the inverse sine of the negative of the square root of 2 over 2 is equal to 7 pi over 4. That is incorrect because it's not in this interval. What you have to do is actually rotate clockwise here. Let me pick a good color here that's going to show up. So this right here, you need a clockwise rotation. So the reference angle there is pi over 4. So this rotation clockwise, this angle is going to be negative pi over 4. So this would be negative pi over 4 as the answer. Now, another way you can do this is a longer way, but essentially what you could do is you could figure out, okay, I'm going to be in quadrant 4, so I want this 7 pi over 4 answer, but I need to put it into this interval since I started here and rotated all the way around by 7 pi over 4. What I have to do is now rotate clockwise by 2 pi. So that's going to be me taking 7 pi over 4 and subtracting away 8 pi over 4 to get my negative pi over 4. So in other words, you're going to go this way, clockwise, by 2 pi. So that's just subtracting 2 pi away. So coming back here and finding a coterminal angle, so ending up right there. So now I'd get the angle that I want, which is going to be negative pi over 4. I think this is a little bit more complicated, but sometimes people need to do that to figure out what's going on. What I always do is figure out what the angle is. So in this case, okay, it's 7 pi over 4. The reference angle is pi over 4, and I know it's negative, so it's just negative pi over 4. I think that's pretty easy to understand. All right, now let's talk about the cancellation properties for sine. So these are some simple rules you can use to quickly evaluate things. So the first one's very straightforward. So you have something like the sine of the inverse sine of x. That's going to be equal to x for x is greater than or equal to -1 and less than or equal to +1. So why do we need this restriction here? So first off, if you consider the outer part here, so the sine of, so this right here is the argument for the sine function. Does it matter what I plug in for the sine function in terms of the domain? No, because it's all real numbers. So I can plug in whatever I want. A negative, 0, positive, whatever I want. The problem actually comes from the inverse sine function. So here, if I look at this x here, what can I plug in for that? Well, remember the domain of the inverse sine function is going to be from -1 to +1. So that's where you have to be careful. If you did something like the sine of the inverse sine of 2, well, you're not going to be able to get an answer there because the inverse sine of 2, you can't type that into your calculator and get an answer. It's just going to give you an error. So what you would want to do is make sure that it's within this interval here. And then if you had a problem like the sine of, let's say, the inverse sine, and then for this, let's say we go with what we just did. So let's say we plug in 1/2. Well, this is going to just give me 1/2. In other words, these guys are just going to cancel away, and I'll be left with this 1/2. If you want to do this the long way, the inverse sine of 1/2, we just saw that was pi over 6. So this would be the sine of pi over 6, which we know is 1/2. So I can just skip this step right here and just go straight to saying that the answer is 1/2. All right, so the next one is a little bit more challenging to understand. So what you want to concentrate on is the first part, so the sine of x. So think about that for a moment. We know that, again, the domain for the sine function, this is not a restricted sine function or anything like that. I can plug in whatever I want for x. It does not matter, any real number. So plug in whatever you want. The result of the sine of x is going to be from -1 to +1. Now, with the inverse sine function, remember, the domain, or what you can plug in, is going to be from -1 to +1. So I'm good to go in terms of plugging things in for the inverse sine function. I'm not going to run into any issues. But the problem is that the range, or the output for the inverse sine function, is only going to be from -pi/2 to pi/2. So if you're in that interval, you can just cancel this with this and say it's equal to x. If you're not, you need to evaluate the sine of x first and then take the inverse sine. So let's look at 2 examples. So the first one is, we have the inverse sine of the sine of -pi/3. So to answer this, the first thing you would do is say, is -pi/3 greater than or equal to -pi/2 and less than or equal to pi/2? Well, this part I know. I know that -pi/3 is certainly less than pi/2 because a negative is always less than a positive. Now, what if you compared this one? Well, the numerators are the same. Forget about the fact that they're negative for a moment. Let's say you had pi/2 and pi/3, and I just put a question mark here. So if I look at this, the numerators are the same, the denominators are different. So same numerator, that means that the larger denominator is going to belong to the smaller fraction. So I can say that this guy right here is greater than this guy right here. But now, if I multiply both sides by -1, that's going to change. So this right here, and this gets flipped. So now this guy, which was the larger fraction, because now that it's negative, it's going to actually be the smaller fraction because it's further to the left on the number line. So that means that -pi/2 is less than -pi/3. So this inequality is going to be true. So that means that I can just say that the answer here, let me slide this out of the way, is just going to be -pi/3. If you go to the unit circle and you wanted to find the sine of -pi/3, again, I'm just looking for an angle in quadrant 4 with a pi/3 reference angle. So that's going to be right here at 5 pi over 3. But again, I'm not thinking about it as 5 pi over 3 because I'm rotating clockwise. So that's my negative pi over 3 angle. So the sine of negative pi over 3 is the same as the sine of 5 pi over 3, the coterminal angle. So that's going to be the negative of the square root of 3 over 2. So if you went through and said, well, what is the inverse sine? So what is the inverse sine of the negative of the square root of 3 over 2? You're going to go right back to that negative pi over 3. So again, if you're in this interval, you can just shortcut all that and just give this as the answer right away. So the answer here is just negative pi over 3. All right, let's look at another one. So this one will give us a little bit of trouble. So we have the inverse sine of the sine of 5 pi over 6. So can we just say the answer is 5 pi over 6? No. And the reason for that is 5 pi over 6 is not in the range of the inverse sine function. We cannot get that as an answer. So because of that, again, what you'd have to do is first find the sine of 5 pi over 6. So coming to the unit circle, here's your 5 pi over 6. And all of you know that that's 1/2. So basically you would have to transform this into the inverse sine of sine of 5 pi over 6 is 1/2. And then we know that this is pi over 6. But again, if we just come back down, you're working here. And this guy is going to be positive. So you're looking in quadrant 1 for an angle with a sine value of 1/2. So you've got that right here, and that's going to be at pi over 6. So that's the angle I'm looking for. So coming back, we just answer pi over 6. So when this guy right here is not in the range, so from negative pi over 2 to pi over 2 of your inverse sine function, you've got to do additional work. First, you're going to do the inside. So evaluate the sine of 5 pi over 6. That gives me 1/2. Then take your inverse sine of 1/2, and that's going to give me pi over 6. All right, now let's move on and talk about finding the inverse cosine function. So the process is exactly the same as what we did for finding the inverse sine function. There's just a few differences in terms of what part of the graph we're going to take in order to create a one-to-one function. So we would start with the graph of y is equal to the cosine of x. So we've studied this graph before. We know that the domain is all real numbers, and the range is from -1 to +1. So let me write here that the domain is going to be the set of real numbers. So from -infinity to +infinity. So I can plug in whatever I want for x there. So a negative, 0, a positive, whatever I want as long as it's a real number. And then for the range, we can see that this is from -1 to +1 with both of those being included. Now again, this function is not a one-to-one function. You can see that from the graph. If I make myself a little horizontal line here, you're going to see that it hits here, and then here, and then here, and then here. And again, this graph continues forever to the right and forever to the left, so it's going to keep hitting over and over and over again. So obviously, this is not the graph of a one-to-one function. So again, what do? Well, we're going to restrict the domain such that we have the same range. So for this one, what we want to actually do is start at 0, so an x value of 0, and then go to an x value of pi. So this is the piece of the graph we want. So this is going to be from 0 to pi. And notice that your range is not going to change. It's still going to be from -1 to +1. So this would create a one-to-one function for us. And to see that more clearly, this is the graph of our restricted cosine function. So this is y is equal to the cosine of x, where x is greater than or equal to 0 and less than or equal to pi. So you can see this would be a one-to-one function now. And let me just write here for clarity that the domain, obviously it's right here, but let's just list it. So this is going to be from 0 to pi, where 0 and pi are both included. And then the range, this is the key here, it's going to be the same as your regular y equals the cosine of x. So it's still going to be from -1 to +1 with both of those guys being included. Now what we can do if we want to find our inverse is reflect this graph across the line y equals x. So if we start with this graph again in purple, this is the graph from the previous page. This is my y is equal to the cosine of x, where x is greater than or equal to 0 and less than or equal to pi. So again, the restricted cosine function, let me just go over this for clarity. So this graph right here, again, you're going from 0 to pi, and the range, and this is the key, is still from -1 to +1. So when you reflect this across the line, y equals x, that's this guy in orange here, you're going to get this graph that's in teal. So this guy right here is the graph for y equals the inverse cosine of x. So if you started with something like, let's say this point right here, which is 0, 1, and you reflect across the line y equals x, you're going to get to this point right here, which is 1, 0, and that's going to be on your inverse. So the x value of 0 becomes a y value of 0, and then a y value of 1 becomes an x value of 1. So those x's and y's are switched. Then if we look at this other point right here, which is pi, -1, again, if I reflect it across the line y equals x, I'm going to get this point right here, which is -1, pi. So here, the x value of pi becomes the y value of pi in the inverse, and then the y value of -1 becomes the x value of -1 in the inverse. To get a better look at this, we can see this graph on its own. So this is for y is equal to your inverse cosine of x. And let me put a little border, just like we did last time. Let me put the y is equal to the cosine of x, where x is greater than or equal to 0 and less than or equal to pi. And again, for this one, we know that the domain, because it's listed specifically right here, is going to be from 0 to pi. Well, notice that the range here for the inverse cosine function is going to be from 0 to pi. So let me write that the range for this one is going to be from 0 to pi. So the domain becomes the range, and the range is going to become the domain. So the range here, the range in this case is going to be from -1 to +1, and you're going to see in the inverse, again, the domain now is from -1 to +1. So let me put that the domain is from -1 to +1. All right, let's look at a few problems now. So here we have y equals the inverse cosine of the negative of the square root of 3/2. So again, a lot of you can immediately say that the answer is going to be 5 pi over 6. But just to go through this the long way, so we understand where this stuff is coming from, what we want to do is think about this y equals the cosine of x. So just start with this, like we did graphically. And we're going to restrict the domain. So x is greater than or equal to 0 and less than or equal to pi. If you go through, this is going to get cut off. So let me just slide down here. We'll come back up. So if you go through and find the inverse of this domain restricted function, you swap the x and the y. So you end up with x is equal to the cosine of y. And of course, this right here, which is the domain, becomes the range. So now you have y is greater than or equal to 0 and less than or equal to pi. So if I have something like, let's say, the negative of the square root of 3/2 is equal to the cosine of y, where y is greater than or equal to 0 and less than or equal to pi, well, when it's written this way, you can say that y is going to be the angle between 0 and pi, where 0 and pi are included, where your cosine value is negative square root of 3/2. Well, again, if you just think about the unit circle and we come down here, well, I'm working from 0 to pi. So now I'm looking here. And if your argument is positive, you're going to look in quadrant 1. And if it's negative, you're going to look in quadrant 2. Again, there are exceptions to what I just said. Just like previously, if you have something like the inverse cosine of, let's say, 1, well, this is going to be 0. So that's going to be a quadrantal angle. If you have the inverse cosine of 0, and that's going to be pi over 2. So that's a quadrantal angle. And then lastly, if you had the inverse cosine of something like -1, well, that's going to be pi. So basically, other than these guys, you can say that if your argument is positive, you're looking in quadrant 1. If your argument is negative, you're looking in quadrant 2. The argument we have, let me get rid of this, is negative. So we're looking for the inverse cosine of the negative of the square root of 3/2. So that tells me I want to look in quadrant 2. So looking in quadrant 2, where cosine values are negative, I see that's going to occur right here. So there's my cosine value of negative square root of 3/2. And the angle that's associated with that is 5 pi over 6. So the result here would be 5 pi over 6. In other words, on the graph of this guy right here, the restricted cosine function, you have the point 5 pi over 6, comma, negative square root of 3/2. So when you get to the inverse cosine function, these guys are going to be swapped. So you're going to have negative square root of 3/2, comma, 5 pi over 6. So when we answer this, we basically just say that, and I think this is cut off too far, so let me just come down here and I'll just answer it formally. I will say that if we have y is equal to the inverse cosine of the negative of the square root of 3/2, then we're going to say that this is equal to 5 pi over 6. All right, let's look at another one. So we have y equals the inverse cosine of negative square root of 2/2. So again, you can work off the unit circle. A lot of you know this off the top of your head, but we're working from 0 to pi. Now, because that guy was a negative argument, so in other words, we had y is equal to the inverse cosine of the negative of the square root of 2/2. Again, when this guy is negative, I want to work in quadrant 2. That's where cosine values are negative. So just find where you have a negative square root of 2 over 2 for the cosine value, and the y there is going to be the associated angle. So basically, I'm going to find that right here. Let me just highlight that. So you have a cosine value of a negative square root of 2 over 2 with your 3 pi. So with your 3 pi over 4. So the answer here for y is just going to be 3 pi over 4. Again, if you look at the restricted cosine function, so y equals the cosine of x, where x is greater than or equal to 0 and less than or equal to pi, well, a point on that graph is going to be 3 pi over 4, comma, negative square root of 2 over 2. So that's a point on the graph. So when we think about the graph of the inverse cosine function, so y equals the inverse cosine of x, well, these x and y values are going to be swapped. So now you have this negative square root of 2 over 2, and then comma 3 pi over 4. So the inverse cosine of negative square root of 2 over 2 is going to give me 3 pi over 4. All right, just like with sine, you have the cancellation properties for cosine and the inverse cosine function when you put those guys together. So basically, if you have something like the cosine of the inverse cosine of x, it's equal to x, but only for x being greater than or equal to -1 and less than or equal to +1. So the reason for that is, again, the domain for the inverse cosine function is going to be from -1 to +1. You can't take something like the inverse cosine of 2. Again, if you plug that into your calculator, you're going to get some kind of error. So what you would do, let's say we had something like, let me just slide down here real quick, the cosine of, let's say the inverse cosine of, let's say something like 1/2. Well, again, this right here would be in quadrant 1. So I'm thinking about where is the cosine value 1/2 in quadrant 1? Well, that's pi over 3. So this, going the long way, would end up being the cosine of pi over 3, and I'm right back to 1/2. So again, if this value satisfies this inequality, so it's greater than or equal to -1 and less than or equal to +1, you can just shortcut this process and immediately give the answer of 1/2. All right, so the other property involved is going to give you a lot of trouble if you're not paying attention. So the inverse cosine of the cosine of x equals x, but this is the key. This is only for x being greater than or equal to 0 and less than or equal to pi. Now, what's causing this? This is your regular cosine function on the inside. So we know that the domain is all real numbers. So really, it doesn't matter what I plug in for x. It could be 0, could be negative, could be positive. It doesn't matter. We know that the range, or the outputs here, are going to be from -1 to +1, and those guys are going to be included. So let me actually just mark this out real quick so we can think about this. So I know that what I'm going to be plugging in here for the inverse cosine function is going to be from -1 to +1, and again, that is the domain of the inverse cosine function. So I'm okay there. I'm never going to violate the domain. So let me erase this, and now let's think about this. When I take the inverse cosine of something from -1 to +1, with those guys being included, I know that my range, or my set of output values, is going to be from 0 to pi. So that's why we have this for x is greater than or equal to 0 and less than or equal to pi. Now, if that was confusing, let me just give you an example here, and hopefully this will make sense. So here we have the inverse cosine of the cosine of 7 pi over 4. Now, 7 pi over 4 is not in the interval from 0 to pi, where 0 is included and pi is also included. If you go to the unit circle, again, this is where we're working right here. So this is from 0 to pi. Now, if we think about 7 pi over 4, that's down here. Okay, so that's not in that interval. So what you'd have to do is say that you have the inverse cosine of the cosine of 7 pi over 4. You need to evaluate this first. So the cosine of 7 pi over 4, that's going to give you square root of 2 over 2. So we're going to say this is the inverse cosine of the square root of 2 over 2. And again, looking in the correct interval here, you see where the cosine value is square root of 2 over 2, that's going to be right here, and that's going to be with pi over 4. So you'd want to answer pi over 4. It is incorrect to say that the answer is 7 pi over 4 because that is not within the range of the inverse cosine function. So you have to be very, very careful with that type of problem. If you had gotten the problem, the inverse cosine of, let's say, the cosine of pi over 4, well, in this particular case, now you're within that interval, so these would just cancel away, and you would say this is pi over 4. Again, if you go through it the long way, which is fine, you can still do that, the cosine of pi over 4 is square root of 2 over 2, and then the inverse cosine of square root of 2 over 2 will get you back to pi over 4. All right, now let's talk about the inverse tangent function. So we're going to use the exact same process that we used with the inverse sine function and the inverse cosine function. So we're going to start off with a graph that we already know about. So that is y is equal to the tangent of x. Now, when you graph this guy, hopefully you've seen this already, you know that you have a series of vertical asymptotes, and that's going to be at odd multiples of pi over 2. So something like this is at pi over 2, and then this guy right here is going to be 3 pi over 2, and this guy right here is going to be 5 pi over 2. And if you were going this way, so this right here would be negative pi over 2, and then this right here would be negative 3 pi over 2. And then this guy right here would be negative 5 pi over 2. So again, what causes that? Well, if you go back to the unit circle, if you look at something like pi over 2 or 3 pi over 2, the cosine value is 0. And this is going to be true for pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so on and so forth. So a lot of books will just say odd multiples of pi over 2. So what happens is, when you look for the tangent of something like that, if the cosine value is 0, you have the sine value divided by the cosine value. And again, if you're trying to divide by 0, that's undefined. So coming back up, that's why you see these vertical asymptotes here. So for the domain, and I'm going to write this in set builder notation. So I'm going to say that it's the set of all x such that x is not equal to, we're going to start with pi over 2 and then just say plus pi n. And here specifically, n is just going to be any integer. So if you added pi to pi over 2, you would get 3 pi over 2. Then if you added, let's say, 2 pi to pi over 2, you would have 5 pi over 2, so on and so forth. Now, in terms of the range, there's no restriction, right? So this is from negative infinity to positive infinity. So for the range, we're going to go, I'll just use interval notation. It's a little bit easier. So from negative infinity to positive infinity. So basically all real numbers. Now, when we look at the graph of y equals the tangent of x, obviously this is not a one-to-one function. It fails the horizontal line test. So let me make a little horizontal line here, and it would hit here, and it would hit here, and here, and here, and here. And of course, this graph continues forever to the right and forever to the left. So it's going to hit over and over and over again. So obviously, this is not the graph of a one-to-one function. So what do we do? Well, just like before, we're just going to take a piece of this graph such that we have a restricted domain, but we keep the same range. So what we've chosen to do in this situation is go from negative pi over 2 to pi over 2, with those values being excluded, because again, tangent of negative pi over 2 or tangent of pi over 2, that's undefined because you'd have division by 0. So this is the piece that we're going to take right here. So that's what we're looking for. And let me just show you that using a better graph. So this right here would be your y is equal to the tangent of x, where x is greater than, and this is strictly greater than, negative pi over 2, and less than, and that's strictly less than, pi over 2. So this is your restricted tangent function. And just like before, if you reflect that across the line, y equals x, you'll get your inverse tangent function. So this right here in orange, this is your y equals, again, the tangent of x, where x is greater than negative pi over 2, and less than pi over 2. And then the graph in green here, this is going to be your y is equal to the inverse tangent, so the inverse tangent of x. So let's go down to this little graph here where things are easier to see. So let's write that this is y equals the inverse tangent of x. And for the domain, you'll see that it's the set of real numbers. So I can plug in whatever I want for x there. There's no problems. So I'm going to say that my domain is just going to be from negative infinity to positive infinity. And if we think about where that comes from, well, think about the range of the restricted tangent function. It's from negative infinity to positive infinity. So when we get the inverse, the domain becomes the range, and the range becomes the domain. So this range here from negative infinity to positive infinity became the domain here of negative infinity to positive infinity. Now, similarly, when we look at the range here, this is coming from the domain of the restricted tangent function, which was from negative pi over 2 to pi over 2, with those guys being excluded. So this is really important. You want a parenthesis here for negative pi over 2. It's not included. And then a parenthesis next to pi over 2 because it's not included. So this value up here and this value down here, they're not included. So you'd have a horizontal asymptote here and also here. So these graphs will approach those values, but never actually touch them. Okay, let's take a look at some problems. So we have y equals the inverse tangent of square root of 3. So again, when I look at something like this, I always go y is equal to the tangent of x, and I'm going to say x is greater than negative pi over 2 and less than pi over 2. And again, I'm just going to swap x and y to find the inverse. So I'm going to say x is equal to the tangent of y, where specifically, again, this was the domain, so now it becomes the range. So y is greater than negative pi over 2 and less than pi over 2. So if I plug in a square root of 3 for x there, so we'd say the square root of 3 is equal to the tangent of y. And again, where y is greater than negative pi over 2 and less than pi over 2. Well, let's think about this for a moment. I'm asking for the angle in the interval from negative pi over 2 to pi over 2 such that the tangent value is going to be the square root of 3. Well, you can use special triangles. We'll go to the unit circle in a moment. If you look at a tangent value of square root of 3, so that's going to be right there. I don't think my highlighter really shows up there. So maybe I can use a different color, like black. I think that might show up a little bit better. So basically, you can see that's going to happen at 60 degrees, or if you want to convert this into radians, that's going to be pi over 3. Additionally, you can always go to the unit circle and use that. The values aren't directly there, but if you look at pi over 3, again, that's in your interval. You're working from negative pi over 2 to pi over 2. The key thing is here that pi over 2 and negative pi over 2 are not included. Okay, so it's not like sine where they are included. Here they're excluded. So if I look at that, that's within the interval. And again, if you look at the tangent of pi over 3, well, really quickly, you can just look at, well, it's the sine of pi over 3, which is the square root of 3 over 2, divided by the cosine of pi over 3, which is basically going to be 1/2. So times the reciprocal, which is 2 over 1. Those 2's cancel, and you get the square root of 3. So that tells me that the inverse tangent, so the inverse tangent of the square root of 3 is going to be pi over 3, because again, it's in this interval. So let's come back, and I'm just going to answer that this guy right here is going to be pi over 3. Okay, let's look at another one. So this will be real easy. We have y equals the inverse tangent of the negative of the square root of 3. So first off, what you could do to solve this problem, the inverse tangent function and the inverse sine function are odd functions. So you could say that this is equal to the negative of the inverse tangent of the square root of 3. And we saw earlier that the inverse tangent of the square root of 3 was pi over 3. So this would be the negative of pi over 3, or just negative pi over 3. So that's the quickest way to solve that, given the fact that you know that the inverse tangent of square root of 3 is pi over 3. Now the other way, let's just do this the longer way, just so we can see it. The first thing is, if I know that y is equal to the inverse tangent of the square root of 3 is going to be equal to pi over 3, we already know that, well then what I can do is go to my unit circle and look for an angle in quadrant 4 where tangent is negative, and I'm going to want a pi over 3 reference angle. So here, I'm going to rotate clockwise to get to right there. So this is not going to be 5 pi over 3. It's going to be negative pi over 3. Again, you can start with 5 pi over 3 if you want and just subtract away 2 pi. So that's 6 pi over 3. And you can get the negative pi over 3 like that if you want. Again, it's up to you how you want to do things. But essentially, you want to make sure that you're in that interval, again, from negative pi over 2 to pi over 2. Let me highlight that real quick. So I'm going to make sure to not touch pi over 2 or negative pi over 2. Those are not included. So as long as you're in this interval, you're going to be good to go. So basically, because the tangent of negative pi over 3 is equal to the negative of the square root of 3, well, because, again, this is in that interval, you can say that the inverse tangent, so the inverse tangent of the negative of the square root of 3, that's going to be negative pi over 3. So coming back up, the answer here, once again, is negative pi over 3. All right, let's look at some cancellation properties with tangent and inverse tangent. So these are very similar to what we saw earlier. So the tangent of the inverse tangent of x is equal to x for any x that's a real number. So that's basically what this is saying. This says x is an element of the real numbers. Whenever you see this r that looks like this means the set of real numbers. So let me write that out. So the set of real numbers. And this right here, if you've never taken a course on sets, this just means is an element of. Now, when we think about the inverse tangent function, remember the domain is the set of real numbers. So I can plug in whatever I want there for x, and the output will be between negative pi over 2 and pi over 2, with those values being excluded. So that means, again, you could just mark this out and say, okay, well, the tangent of between negative pi over 2 and pi over 2, that's always going to be defined, so I won't really have any issues there. So I can just basically cancel things away and say that I just have x. So if you wanted to see an example of that, you could just quickly do something like the tangent of, let's say, the inverse tangent of, let's just go ahead and do something like maybe the square root of 3 over 3, something like that. I think most of you know that the inverse tangent of the square root of 3 over 3 is going to be pi over 6. So this would be the tangent of pi over 6. And again, the tangent of pi over 6 is going to get me back to the square root of 3 over 3. So you could have just shortcutted the process and just said the answer is square root of 3 over 3. All right, let's look at the other one, and this one is where people get into trouble. So the inverse tangent of x is equal to x for x is greater than negative pi over 2 and less than pi over 2. So let me walk you through this one. So basically, let's start off with the tangent of x, so the inside part here. We know that for this guy right here, x cannot be pi over 2, 3 pi over 2, 5 pi over 2. So you could say pi over 2 plus pi n, where n is any integer, or you could say something like odd multiples of pi over 2, whatever you want to do. But basically assuming that this guy right here, you don't plug in something that gives you undefined as a result, well, then we know that the range for the tangent of x is going to be all real numbers. So assuming that you didn't plug in something that violated the domain to where you got undefined, the result of this guy right here would be all real numbers. Now, when you take the inverse tangent, again, the domain is all real numbers. And when you plug in all real numbers for this guy, you're going to get basically between negative pi over 2 and pi over 2 as a result. So that's why we say this is for x is greater than negative pi over 2 and less than pi over 2, because again, that's from the range of the inverse tangent function. So let's look at an example. So here we have the inverse tangent of the tangent of 4 pi over 3. So the tangent of 4 pi over 3, that's defined, but it's not within that range from negative pi over 2 to pi over 2. So coming back to the unit circle, again, thinking about from pi over 2 to negative pi over 2, again, those guys are excluded, so I'm trying to stop short there. And maybe I touched there, so let me try this one more time. I want to make that crystal clear that pi over 2 and negative pi over 2 are not included. So you're looking at this angle right here, which is 4 pi over 3. So that's not in that interval. So what you would have to do is first say that I want the tangent of 4 pi over 3. Now this has a pi over 3 reference angle, and you're in quadrant 3. So we know that this would be equal to the tangent of pi over 3, because again, the tangent values are positive in quadrants 1 and 3. So essentially, if I look at this guy right here, the tangent of pi over 3, it's going to be the same as the tangent of 4 pi over 3. Again, the period for tangent is going to be pi. So the tangent value is going to be the same there. So this is going to be equal to, as we saw earlier, the square root of 3. So essentially, when we solve this problem, if we say something like the inverse tangent of the tangent of 4 pi over 3, what you need to do is the tangent of 4 pi over 3 first. So this is the inverse tangent of, again, that would be square root of 3. So square root of 3. And then this equals what? Well, where's the tangent value square root of 3 in this interval here? Well, it's going to be at pi over 3. So that puts me right back to pi over 3. So you got to be really careful with these types of problems. Now, again, if you had gotten the problem as something like, let's say, the inverse tangent of, and let's go tangent of negative pi over 3. We saw that earlier. Well, this guy right here is in your interval. So we know that that's going to be right here, again, rotating. Let me do this in a different color. So rotating clockwise like that. So that's my negative pi over 3. So I can just take that in this case. That'll be the answer. So this is just negative pi over 3. All right, now let's look at some problems that deal with the inverse cotangent function, the inverse secant function, and the inverse cosecant function. So these problems are pretty easy if you already understand the inverse sine function, the inverse cosine function, and the inverse tangent function. You can actually convert them over and use those guys to get your solution. So let me start with y is equal to the inverse cotangent. Let me make that a little bit cleaner there. Of x. If you're looking this up online, or if you're using a textbook that's different from mine, you might see a different graph. And the reason for that is very simple. When you derive this guy, you start off with y equals the cotangent of x. So we know that that guy right there is not a one-to-one function. We also know it's not defined for pi n, where n is any integer. Because if you have something like 0 or pi or 2 pi or 3 pi, your sine value is going to be 0, and you'd have division by 0, which is undefined. So what you could do is take a piece of that guy, let's say from 0 to pi, where 0 and pi are not included. And basically, if you restrict that domain there, you're going to get a one-to-one function. And if you reflect that across the line y equals x, you're going to get this graph here. So in this case, the domain is now going to come from the range of that guy. So you're going to have all real numbers. So from negative infinity to positive infinity. And then the range, again, is coming from the domain of that guy. So from 0 to pi, where 0 and pi are not included. So the way you can evaluate this is to say it's x is equal to the cotangent of y, where y is greater than 0 and less than pi. So again, 0 and pi are not included. Okay, let's look at a quick little problem, and I'm going to show you an issue that's going to come up if your argument is negative for the inverse cotangent function. So we have y equals the inverse cotangent of negative square root of 3. So first off, I know that basically I can say that this is x is equal to the cotangent of y, where y is greater than 0 and less than pi. Well, the x here is the negative of the square root of 3. So basically I'm asking for what angle between 0 and pi is going to have a cotangent value that's negative square root of 3. Again, if you come back to this little table, some people have this for cotangent already, but I'm just going to use this one. If you look at this value right here for 30 degrees or pi over 6 radians, well, the tangent, so the tangent of pi over 6 is going to be the square root of 3 over 3. So that tells me the cotangent of pi over 6 is going to be, again, take the reciprocal of this, so 3 over the square root of 3. Now you could do this in different ways. You could rationalize the denominator, or a quicker way would be to say that 3 is the square root of 3 times the square root of 3. So you could do it that way if you want. So this would cancel and you get the square root of 3. So pi over 6 would be my reference angle in quadrant 2. So in quadrant 2, what angle has a reference angle of pi over 6? Well, it's going to be 5 pi over 6. So this right here would just be equal to 5 pi over 6. Again, it's got to be within this interval for you to give that answer. Another way you could have done this is by using the inverse tangent function. So let's say you started with the inverse cotangent of your negative square root, and let me make that a little bit better, of 3. Can you say this is equal to the inverse tangent, so the inverse tangent of the reciprocal of this, so the negative of 1 over the square root of 3, if you rationalize the denominator, that is the square root of 3 over 3? Well, the answer to that question is no. You need to issue a little bit of a correction because this right here, so this right here, is going to give you something in quadrant 4 rotating clockwise. So this guy right here would give you this guy right here. So this would be negative pi over 6. So a pi over 6 reference angle in quadrant 4, and you've got to rotate clockwise. But the answer is actually going to be right here at 5 pi over 6, because with the inverse cotangent function, I'm working from 0 to pi. So I'm working right here. So what you would want to do is make yourself a little correction and add pi. So I'm going to add pi so I can swing around right there. And that's going to give me the correct answer. So I'm going to add pi to issue a correction here. And so this would be negative pi over 6 plus pi. Let's write that as 6 pi over 6. And so that would be equal to the 5 pi over 6. That is the correct answer. So if you're using your calculator, you need to be aware of this. If your argument is positive, you're going to be in quadrant 1, so you're okay there. You don't have to issue a correction because the inverse tangent of something that's positive is going to give you something in quadrant 1 as well. But if this guy is negative, you're getting something in quadrant 4 for the inverse tangent function, and you're getting something in quadrant 2 for the inverse cotangent function, so you have to be very, very careful and issue a correction there. Now, if you do the inverse cotangent of 0, you're just going to end up getting pi over 2 as an answer, so that's one you just need to memorize. All right, so the next graph is going to be for the inverse secant function. So y equals your inverse secant of x. So if you look at the domain, so this one, let's just do it in interval notation. So from negative infinity to negative 1. So let's go from negative infinity up to and including negative 1. So again, this is included here. You have a point there. This would be negative 1 comma pi. And then basically the union with positive 1 is included and out to positive infinity. So basically the values between and not including negative 1 and positive 1, those are excluded from the domain. So then for the range, let me write that down here. So for the range, you can see that this guy is going to be from 0 to pi, where basically this pi over 2, let me write this in so this is not confusing. So this is pi over 2 here. That's not going to be included. Let me write up here that this is going to be pi. So the range you're going to have, let me move this up a little bit so it fits, basically from 0 and including 0, going up to and excluding pi over 2, and then the union with, you're going to have, again, pi over 2 is excluded, going up to and including pi. Okay, let's take a look at a little sample problem. We're going to convert this over and solve it very quickly. So here we have y equals the inverse secant of square root of 2. So essentially what I'm going to do is actually say that this is equal to the inverse cosine of, I'm just going to take the reciprocal of this, so 1 over the square root of 2. So if you rationalize the denominator there, this becomes the square root of 2 over 2. And so this, we know, is going to be pi over 4. So for these problems, you don't have to issue a correction. Basically, you're just going to key it in like this. So if you have the inverse secant of something, you basically are going to take the reciprocal of that value and have the inverse cosine of that, and that's how you're going to get your answer. All right, let's take a look at the inverse cosecant function. So again, with the inverse cotangent function, the inverse secant function, and the inverse cosecant function, it might look different in your book or your online resource. So just telling you that in advance. So this guy right here for the domain, pretty easy to see. Basically, it's going to be from negative infinity up to and including negative 1. So this right here, this is a point that's included. So this would be negative 1, comma, negative pi over 2. And then basically the union with this point right here, this is positive 1 comma pi over 2. So basically, you're going to take from positive 1 out to positive infinity. So that's your domain. And then in terms of your range, well, that's going to be from negative pi over 2 to pi over 2, where you're going to exclude 0. So basically, let's say we have from negative pi over 2, and then we're going to go up to and exclude 0. And then the union with, again, we're excluding 0, and we're going up to pi over 2. So pi over 2 and negative pi over 2 are included, but 0 here, that's going to be excluded. Okay, let's look at a problem. So here we have y equals the inverse cosecant of a negative 2 times square root of 3 over 3. Again, all you have to do for this problem is say this is equal to, I'm going to use my inverse sine function. So my inverse sine function, and I'm just going to take the reciprocal of the argument here. So it's going to be the negative of 3 over 2 times the square root of 3. So let me go ahead and write this as the square root of 3 times the square root of 3. And I'm going to cancel this with this. And so this becomes the negative of square root of 3 over 2. So the negative of the square root of 3 over 2. And this one, you might benefit a little bit from the unit circle. So again, with the inverse sine function, you're working in quadrants 1 and 4. If you're in quadrant 4, you've got to rotate clockwise. So where is my sine value? Negative square root of 3 over 2. It's going to be right there at 5 pi over 3. But again, you've got to rotate clockwise. So the reference angle there is pi over 3. So you'd say this is negative pi over 3. So that's what you want for your answer. Let me just move this down here. This would be equal to negative pi over 3. So these types of problems are really easy if you already understand the inverse sine function. All right, now let's move on and look at some typical examples for this section. So what if you see something like the inverse sine of the tangent of negative pi over 4? Well, the idea for this type of problem is to evaluate this part first. So what's inside, or what's going to be the argument for the inverse sine function. And so you would say, what is the tangent of negative pi over 4? A lot of you know that's negative 1. But again, just in case you don't, you're going to look at your unit circle and you're going to say, well, where is negative pi over 4? Well, again, I'm looking in quadrant 4 and I want a pi over 4 reference angle. So that's going to be right here at 7 pi over 4. But what I'm doing is I'm rotating clockwise. So I want this guy right here. Again, rotating clockwise. Let me do this in a different color here so this shows up really well. So this right here is the angle that I'm looking for, negative pi over 4. Now, of course, this is coterminal with 7 pi over 4. So if I want the tangent of negative pi over 4, I can just say that's equal to the tangent of this 7 pi over 4, and I could just grab that from the unit circle. Again, here you want the sine value, which is negative square root of 2 over 2, divided by the cosine value, which is square root of 2 over 2. So I'm dividing opposites, so I'm going to get negative 1 as a result. So coming back up, this would be the inverse sine of this right here is negative 1. And again, a lot of you already know this is going to be negative pi over 2. But again, because we just started with this section, let me get rid of this. You're thinking about where your sine value is negative 1. So that's going to be right here. But again, that's not in the interval of the inverse sine function. So I can't give this 3 pi over 2 as a result. So what I want to do is think about rotating clockwise. So clockwise like this. And basically, that's going to give me an angle that is negative pi over 2. And of course, that's coterminal with 3 pi over 2. So the sine value is going to be the same. It's going to be negative 1. So coming back up, I want to give an answer here that's going to be negative pi over 2. All right, let's look at another common type of problem for this section. So you might see something like the tangent of the inverse sine of 3/4. So what can you do for this type of problem? Well, of course, you could pull out your calculator and you can key in the tangent of the inverse sine of 3/4, and it will give you an approximation. But in most cases, you're asked to find the exact value. So for that, what I recommend is to make a little substitution for this part right here. So the inside right here, which is the argument for the tangent function, you're going to let something like, let's say, theta be equal to this guy right here. So the inverse sine. So the inverse sine of 3/4. And so since theta is equal to this, I can say that now I'm trying to figure out what is the tangent of theta. So I'm just going to say for right now, this equals what? So let me slide down and let's think about, do we have enough information to figure out what the tangent of theta is? Well, of course we do. First off, we know that if theta is equal to the inverse sine of 3/4, then we can say, so I'm going to put then, we can say that the sine of this angle theta is equal to, my sine value is 3/4. Again, if the sine of theta is 3/4, well then the inverse sine of 3/4 is going to get me back to theta. Now we also know that if sine is positive, I'm going to be in quadrants 1 or 2. But specifically here, because I'm working with this inverse sine function and the argument is positive here, I know I'm going to be in quadrant 1. This is always going to be true unless you have the inverse sine of positive 1, which is pi over 2, that's a quadrantal angle, but that's the only exception. So for this particular case, I know that theta is in quadrant 1. And I went over my border a little bit. So let me put the border like this. And so now I can go back to what I talked about earlier on in the course when we said that, okay, if the sine of theta is equal to 3/4, well, that 3 is going to be your opposite or your y, and that 4 is going to be your hypotenuse or your r. So if I want to figure out the tangent of theta, remember this is going to be your y or your opposite over your x, which is your adjacent. So I already know that y is 3. So I can just plug that in right now and say this is 3. And I just need to figure out what is x. So you're going to use your Pythagorean theorem. You don't have to do this, but I went ahead and made a little sketch. So remember, for the Pythagorean theorem, you have x squared plus y squared is equal to r squared. So in this case, we know that the y, or the opposite side, is 3. So I'm just going to plug that in there. We know that the r, or the hypotenuse, is 4. So I'm going to plug that in there. We're going to find that the x, or the adjacent side, is going to be square root of 7. Right now, I don't know that. I'm going to solve for that. So here I would have x squared plus 3 squared is 9. And this equals 4 squared, that's 16. So what I'm going to do is subtract 9 away from each side of the equation. And so this right here is going to cancel. You'll have x squared is equal to 16 minus 9 is 7. Now, by the square root property, you would say that x is equal to plus or minus the square root of 7. Now, I'm in quadrant 1, where x values are positive, so I don't need the plus or minus here. X is going to be the principal square root of 7. So now I know that the adjacent side here, or the unknown x, is going to be square root of 7. And just coming back up, I'm going to put that this right here is the square root of 7. And let me move this over here. I can just answer that this right here is 3 over the square root of 7. So 3 over the square root of 7. And of course, you would want to rationalize the denominator. So times the square root of 7 over the square root of 7. So my final answer here for the tangent of the inverse sine of 3/4 is going to be 3 times the square root of 7 over 7. All right, now let's look at another type of problem. So this one is just a little bit more tedious than the previous problem. So we have the sine of the inverse sine of 1/2 plus the inverse tangent of -3. So for sure, you're going to get a problem like this in your textbook. And what you want to do is start off by asking, can I replace anything in my problem? So in other words, I know that the inverse sine of 1/2 is pi over 6. Let me just come down to the unit circle. Again, this is new for us. I know a lot of you already know that. But again, I'm working from negative pi over 2 to pi over 2. And I am asking the question, what is the inverse sine? So what is the inverse sine of 1/2? So I'm looking for a sine value of 1/2, so that's going to occur right here. And so what I want for the associated angle is pi over 6. So the sine of pi over 6 is 1/2. So the inverse sine of 1/2 is going to be pi over 6. Again, it's got to be in this interval from negative pi over 2 to pi over 2. So this right here is going to be pi over 6. So coming back up here, I'm just going to replace this with pi over 6. So this is the sine of your pi over 6 plus, now this one, I'm going to make a substitution for it. Let me just write it in for right now. So the inverse tangent of -3. Okay, so just like in the previous problem, we have something here where we're going to make a little substitution. So you have the inverse tangent of -3. Let me slide down here real quick. And I'm just going to put that we are going to let something like beta be equal to the inverse tangent of -3. So what I'm going to do is replace this right here with beta. So I'm going to say that now I'm looking for the sine of pi over 6 plus beta. Remember, when we think about this beta here, if we let beta be equal to the inverse tangent of -3, that tells me that the tangent of beta is equal to -3. Now, where is beta? Remember, the inverse tangent function is going to give you something in quadrant 4, rotating clockwise if the argument is negative. So that tells me, let me put a little border here, that beta is in quadrant 4. Okay, so we're going to use that in a little while. So the first thing is I'm going to grab this and copy it, and I'm going to go to another page, and let me paste this in here. When you have the sine of a plus b, in this case it's pi over 6 plus beta, but the sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. This is your sum identity for sine that we talked about earlier in the course. So we're going to say that this sine of, you have this pi over 6 plus beta, this is equal to the sine of the first guy, which is pi over 6, and then times the cosine of the second guy, which is beta, and then plus the cosine of the first guy, which is pi over 6, and then times the sine of the last guy, which is beta. So the sine of beta. So this equals what? In terms of the sine of pi over 6, we know that's 1/2, and the cosine of pi over 6, that's square root of 3 over 2. Most of you don't need this at this point, but again, if you don't have a unit circle, here's pi over 6, so the sine value is 1/2, and the cosine value is square root of 3 over 2. So let me come back up here. So the sine of pi over 6 is 1/2, and then times your cosine of beta, and then plus the cosine of pi over 6 is the square root of 3 over 2, and then times your sine of beta. So what I need to do is I need to figure out what is the cosine of beta. So the cosine of beta is, again, that's your adjacent over your hypotenuse, or we say the x over the r. And then what is the sine of beta? So the sine of beta is equal to your opposite over your hypotenuse, or your y over your r. Well, let's go back up, and let's remember that we know that the tangent of beta is equal to -3. You can go ahead and say that this is -3 over 1. So this right here is the y value. It's going to be -3 because, again, we're in quadrant 4. So the y values are going to be negative, and the x values are going to be positive. And this right here will be your x value, so that's +1. So let's come down here, and I'm just going to write in that the tangent of beta is equal to -3 over 1. Again, this is your y, and this is your x. So we can come through here and say that x is 1, so I know this is a 1, and then y is -3, so I know this is -3. Now, how do we get r? Again, go back to the x squared plus y squared equals r squared. And again, you can make a sketch. It's not necessary, but you can do it. So let's put x squared plus y squared equals r squared. We're going to find out that r, or this hypotenuse here, is square root of 10. But to get that, x, or your adjacent, is going to be +1. So this is 1 squared plus your y, or your opposite, is going to be -3. Remember, you're in quadrant 4, so the y values are negative. So this is -3. Make sure to wrap that. And this is going to be squared. And this equals your r being squared. So that's going to be for your hypotenuse, that guy being squared. Okay, so this is pretty straightforward. 1 squared is 1. And then plus -3. Again, this is wrapped, being squared. That's +9. And this equals r squared. So you get r squared is equal to 10. Again, by the square root property, you get r is equal to plus or minus the square root of 10. Now your r is always positive, so this is just the principal square root of 10. So your x is 1, your y is -3, and then your r is going to be square root of 10. So coming back up, if I know that r is square root of 10, I'm just going to replace that here. So this is square root of 10, and then this right here is square root of 10. Okay, I'm going to get rid of this. We don't need this anymore. And I'm going to rationalize the denominator in each case. So this is times the square root of 10 over the square root of 10. So this equals the square root of 10 over 10. And then here times the square root of 10 over the square root of 10. So this equals negative 3 times the square root of 10 over 10. Okay, so I just need to replace here and here. So what I'm going to have, let me put equals. You have 1/2 times the cosine of beta is the square root of 10 over 10. And then plus you have the square root of 3 over 2 times the sine of beta. That's negative 3 times the square root of 10 over 10. So this equals, I would just multiply and say this is the square root of 10 over 20. Just multiplying 1 times the square root of 10, that's square root of 10, and 2 times 10 is 20. So then you have plus, you have the square root of 3 times negative 3 times square root of 10. So let's go ahead and write that as a negative here. And I'll put 3 times the square root of 30. Square root of 3 times square root of 10 is square root of 30. And you really can't simplify that any further because 30 is 6 times 5, 6 is 2 times 3, so you really can't do anything more with that. So then this is over. 2 times 10, that's going to be 20. So what I'm going to do is write this with a common denominator. So I'm going to say this is the square root of 10 minus 3 times the square root of 30 over the common denominator of 20. All right, so let's come back up here to the top. And let me just paste this in. So I'm going to say that the sine of the inverse sine of 1/2 plus the inverse tangent of negative 3 is going to be equal to this square root of 10 minus 3 times square root of 30 over 20. In this lesson, we want to talk about solving trigonometric equations using linear methods. All right, so let's start off with the easiest possible scenario. We're going to solve some trigonometric equations, again, with these linear methods. Let's say you had something like 2 plus 4 times the sine of theta is equal to 4. So what we're trying to do here, we're trying to find values of theta, okay, that I could plug in here and make the equation true. Now, before I go through this, let's just look at something from basic algebra, so we'll remember this. If I had something like 2 plus 4x is equal to 4, how would I solve this? Well, I'm trying to find values for x that make the equation true, right? So I would first try to isolate x, so I would subtract 2 away from each side of the equation. And so this is going to cancel. I would say 4x is equal to 2, divide both sides by 4, and I get that x is equal to 1/2, okay? So I plug a 1/2 in there, and basically you have what? You have 2 plus, basically 4 times a half is 2, so 2 plus 2 gives me 4, so that is the correct solution. With this guy, it's not as straightforward. It's not as easy because remember, you're plugging in an angle measure there. Sine of that guy would give you a number, okay? So you're looking for sine of some value. I can already tell you that this needs to be a half for this to be true. So where is sine of theta equal to a half? Okay, that's what you're going to be looking for. But to solve this fully, let me subtract 2 away from each side of the equation. This cancels. We get 4 times the sine of theta is equal to 2. We divide both sides by 4. And basically, we're going to get that the sine of theta, again, is equal to a half. Okay? So from this guy right here, this is where you need to basically do a little bit of detective work. Okay? There are so many ways to solve this. It's not even funny. You might want to use a calculator and use your inverse sine function. You might want to use the unit circle. There's a lot of different things that you could do. You could use the special triangles that you remember, all kinds of ways. So let me talk about 2 ways that you can solve this. First, let's think about the unit circle approach. So if you are lucky and you get an easier problem where basically you can find this from the unit circle, you can go to the unit circle. If I'm looking for sine of theta is equal to a half, well, you can look for the y coordinate and find out where it's a half. Okay, so for 30 degrees or pi over 6 in terms of radians, the y coordinate is a half, right? So that tells me that sine of 30 degrees is equal to a half. Then also, I know that sine is positive in quadrant 2. So remember, when we think about reference angles, if the reference angle is 30 degrees, then sine of that guy is also going to be a half, right? So where would I have a reference angle of 30 degrees? Well, with 150 degrees, right? Because 180 degrees minus 150 degrees, the reference angle will be 30 degrees. So sine of 150 degrees, and I'm messing up my writing there, so sine of 150 degrees would also be a half, right? And you can see that here. This is a half, this is 150 degrees, or 5 pi over 6 if you're talking about radians. Now, when you talk about solutions over the interval from, if you're thinking about 0 to 360 degrees, your solutions would be 30 degrees and 150 degrees. But when you think about a general solution, remember, when you think about sine and cosine, the period is 360 degrees or 2 pi, okay? So that means if I started here and I rotated around 360 degrees, well, instead of 30 degrees, now I'd have 390 degrees, and sine of 390 degrees would also be a half, okay? If I added 360 degrees again, then sine of, in that case, 750 degrees would also be a half, so on and so forth. Same thing with 150 degrees. If I add 360 degrees, I'm going to be at 510 degrees. Sine of that guy would be a half as well, okay? So let's take that information and come back here and give a solution, okay? So first, let's pretend we're restricting the domain. So 0 to 360 degrees, or again, you might see this in terms of radians. So you might see 0 to 2 pi in terms of radians. Whatever you get, you want to match that in terms of your answer, okay? So if you get degrees, put degrees. If you get radians, put radians, okay? So in this case, I'll just do both. So in this particular case, I'll say that theta is equal to, we had 30 degrees and then also 150 degrees. And again, the reference angle for both of those is going to be 30 degrees. And then if we look at, in terms of radians, we could say theta is equal to pi over 6. This is 30 degrees in terms of radians. And then 5 pi over 6. And this is 150 degrees in terms of radians. Now, this is the solution for the restricted domain. If you want a general solution, so let me put the general solution. Okay, so this is going to keep working as we either rotate clockwise or counterclockwise. So remember, if you go 360 degrees, doesn't matter which direction. If you go negative direction, so you're going clockwise, or you go the positive direction, so you're going counterclockwise, you're going to keep getting these guys. Okay, so I'm going to start with, let me make some set braces here. Okay, this is typically how you'll see it. I'm going to take this solution. You could do it degrees or you can do it radians. I'll do both. So 30 degrees plus the 360 degrees. Okay, when you go around, again, you're going to get that same value, and then times n, where n is just any integer. Okay, and then I'm going to do 150 degrees and then plus this 360 degrees. Let me slide all of this down because it's not going to fit. So let me move this down and let me put this comma back where it should be, right there. Okay, so this, I'll close my set braces and I forgot my n. So let me put the n there. Okay, so that's your general solution in terms of degrees. With radians, you would say pi over 6 plus, remember, 360 degrees is just 2 pi. Okay, so I'm going to put 2 pi n, and then I'll do 5 pi over 6 plus 2 pi n. Okay, so there's your general solution. There's your solution for having this domain restriction, okay, where basically you're between 0 and 2 pi, or if you think about this in terms of degrees, 0 and 360 degrees. Now, let's talk about another way that you could have gotten this answer. In a lot of cases, especially harder cases, you're not going to be able to use the unit circle, okay? So what you want to do is use your inverse sine function. So let me use a fresh sheet here. Let's say I looked on my calculator and I did inverse sine of, in this particular case, we were looking at a half, okay? So you punch this into your calculator, and we already know you're only going to get one value, right? You're just going to get 30 degrees, okay? But again, if I think about sine of theta is equal to 1/2, there's an infinite number of angle measures there that's going to be true for this. And if I have one of them, then I can find all of them, again, because where is sine positive? It's positive in quadrants 1 and 2, okay? So I have the answer from quadrant 1. I have my answer from quadrant 1. It's going to be 30 degrees. And again, it repeats. So 360 degrees in either direction. So if I go plus 360 degrees or if I go minus 360 degrees, I'm going to, again, run into another solution. But in quadrant 2, I just need an angle where the reference angle is 30 degrees, okay? So again, that's going to be found by taking 180 degrees. So I would take 180 degrees, okay, minus 30 degrees, and that gives me 150 degrees, okay? So this is the angle I'm looking for. So in quadrant 2, I get 150 degrees. So that's another way that you could solve this. You could also use special triangles if you wanted to, okay? So there's a lot of different ways to think about this guy. Okay, let's look at another example. So we have the cosine of theta now instead of the sine of theta. So we have -4 minus 4 times the cosine of theta is equal to -3 minus 2 times the cosine of theta. And again, if you were working with this, let's say you had something like -4 minus 4x is equal to -3 minus 2x. Well, I'd want to get all the terms with x on one side, all the numbers on the other. Same thing here. I'm going to get all the terms with cosine of theta involved on one side, all the numbers to the other. So let me add 4 to both sides, okay? And let me add 2 cosine theta to both sides, okay? And basically, we see that over here, this is going to cancel. over here, this is going to cancel. So I have negative 4 plus 2, which is negative 2, times the cosine of theta is equal to negative 3 plus 4, which is 1. Okay. To isolate this guy, I'm going to divide both sides by negative 2. And I'm basically going to find that the cosine of theta is equal to negative 1/2. Again, another easy problem where you can get this from the unit circle. But let's go ahead and use our inverse cosine function. So let's go cosine inverse of negative 1/2. And let's do a little bit of detective work. If you punch that in on a calculator, you're going to get 120 in terms of degrees. Okay. So let me erase this so I can drag this up. We'll have a little bit of room. Okay. Let me bring this up. And let's think about this. So I have 120 degrees there. Okay. So in terms of the reference angle for that, remember, if you're in quadrant 2, the reference angle is 180 degrees minus your angle, which is 120 degrees. So this is going to be 60 degrees. So this is my reference angle, okay? So what I want to do now, again, because this is negative here, cosine is negative in quadrants 2 and 3. So I have my quadrant 2 solution. My quadrant 2 solution is 120 degrees. For my quadrant 3 solution, I want to think about an angle in quadrant 3, okay, that has a reference angle of 60 degrees. How do I find that? Well, in quadrant 3, I would want to take 180 degrees, and I would want to add to that 60 degrees, which is my reference angle, okay, which would give me 240 degrees. Okay, this is 240 degrees. And the reason that works is, again, if I had a 240 degree angle, and I said, hey, what's the reference angle? You would subtract 180 degrees to get 60 degrees, okay? So this is my answer in quadrant 2. This is my answer in quadrant 3, okay? Now, again, if you wanted a general solution, so let's pretend that first you got a domain restriction from 0 to 360 degrees, like this. And then also in terms of radians, we have 0 to 2 pi, okay, like this. So for the degrees, you would just put that theta is equal to 120 degrees, okay, and then 240 degrees. And then for your general solution, again, all you have to do in this particular case is, let's use some set braces here, and we'll say 120 degrees plus 360 degrees times n, where n is any integer, and then you'd have 240 degrees plus 360 degrees times n, where n is any integer. Okay, if you want to do this in terms of radians, we can do that as well, no problem. So we would say something like theta is equal to, within this domain, 120 degrees is going to be 2 pi over 3, okay? And then we also have 240 degrees, which is going to be 4 pi over 3, okay? For the general solution, I just go 2 pi over 3 plus 2 pi n, and then I go 4 pi over 3 plus 2 pi n. Okay, so again, the period for cosine and sine is 360 degrees or 2 pi in terms of radians. So that's what you want to add. So you have 2 pi, and then n is just any integer. Okay, so that's how you want to do that. Now, if you wanted to solve this more quickly, especially if an easy problem, use the unit circle. So where's the x value, negative 1/2? Well, again, you come over here. Negative 1/2 is 120 degrees or 2 pi over 3 radians, okay? And then also 240 degrees or 4 pi over 3 radians, you got negative 1/2 again is the x value, okay? So this is the quickest way to do it. The other way is something you need to understand because in some situations you're not going to be able to use the unit circle. They're going to at some point give you harder problems. Okay, let's look at one more problem, and this one has tangent involved. Remember, the period for tangent is now going to be pi, okay, or 180 degrees. So you have to keep that in mind here. So if I have something like the negative of the square root of 3 plus 4 minus tangent of theta is equal to 4 plus 8 times the tangent of theta, well, immediately I can just get rid of the 4 from each side, right? Same thing on each side, just get rid of it. And what I want to do now, let me go ahead and subtract 8 times the tangent of theta away from each side of this guy. So I forgot my 8. So minus 8 times the tangent of theta, okay? So this will cancel out over here, okay? And I'm just going to add 3 times the square root of 3 to both sides. So what I'm going to end up with is, you can put a negative 1 there. You'll say you have negative 9 times the tangent of theta is equal to 3 times the square root of 3. Divide both sides by negative 9, okay? Let me scroll down just a little bit, and I'll say that I have the tangent of theta is equal to, the 3 is going to cancel with the 9. This is a 1. This is a 3. So let's say the negative of the square root of 3 over 3. Okay. So now with tangent, it is a little bit more challenging to think about these. You could use your special triangles in this particular case and just think about the square root of 3 over 3. The tangent of 30 degrees is square root of 3 over 3. So let me just write this over here. The tangent of 30 degrees is equal to the square root of 3 over 3. So again, I would say that tangent is going to be negative where? Let me draw this out here so we remember this. So we remember all students take calculus. So tangent is negative in quadrants 4 and 2, okay? So let's think about this. In quadrant 2, where would I have a 30-degree reference angle? Again, if I take 180 degrees and I subtract off 30 degrees, that gives me 150 degrees, okay? My reference angle here for a 150-degree angle would be 30 degrees. So my value here, if I did tangent of 150 degrees, because it's negative, I would get the negative square root of 3 over 3, okay? So let me erase this for a second. Let me just put one answer here. So theta here would be 150 degrees, or again, if you want to write this in terms of radians, this is 5 pi over 6, okay? Whatever you want to do. So let me erase this for a second. Let's think about in quadrant 4. So remember I said the period when you work with tangent is 180 degrees. So I can just add 180 degrees to this, okay? So 150 degrees plus 180 degrees is going to be 330 degrees, okay? Also, what you could have done, and this is 11 pi over 6 in terms of radians, also what you could have done is, again, look for a 30-degree reference angle in quadrant 4. So in quadrant 4, I would just go 360 degrees minus 30 degrees is going to give me 330 degrees. So this is the angle I'm looking for. All right, so obviously these would be your solutions if you had a domain restriction, okay? But if you didn't have a domain restriction, let me just write this over here. So this is 0 to 360 degrees, and this one is 0 to 2 pi, okay, in terms of radians. If you didn't have a domain restriction, you have to be careful because a lot of students will come through here. They're used to working with sine and cosine. So they go 150 degrees plus 360 degrees times n. Okay, this is actually wrong. Okay, the period for tangent is 180 degrees. So you want to put 180 degrees like this. Now, do you need to list 330 degrees plus 180 degrees times n? No, you do not. And the reason for this is if you go back to this one right here, let's say n is 1. Well, you're basically adding 150 degrees to 180 degrees, you get to 330 degrees. So you don't need to put this guy in here, it's just overkill. Okay, just put it like this and be done with it. Okay, then the other one over here for radians, you're just going to put 5 pi over 6 plus you're going to do pi, okay, which is 180 degrees in terms of radians, times n. Okay, that's all you need to do because again, if you added basically one, you could get a common denominator and say it's 6 over 6. So if you had 6 pi over 6 plus 5 pi over 6, you would get 11 pi over 6, okay? So again, it's overkill to list both of them in that case. You just want to list it like this as simply as you possibly can. In this lesson, we want to talk about solving trigonometric equations by factoring. All right, so now we're just going to look at the next scenario. We already talked about how to solve these basic trigonometric equations using linear methods. Now we're just going to be factoring. So we have 3 times cosine theta plus 2 times cosine squared theta equals -1. So a very easy problem. You want to get this. If you see something with a squared term in it, you want to think about factoring right away. Okay, that's usually how you're going to solve that. And you want to think about getting it in the form of ax squared plus bx plus c equals 0. Okay, remember this is a quadratic, and you're able to solve this by factoring and then setting each factor equal to 0, right? That's the 0 factor property. So I'm going to do the same thing here. I'm going to move this to the left, basically. So I'm going to say I have 2 times cosine squared theta, and then plus this 3 times cosine of theta. And I can add 1 to both sides of the equation. So say plus 1 and this equals 0. So if I can factor the left side, again, I can use that 0 factor property. There is a tremendous roadblock to factoring this when you first start. I don't know why it is, but when I work with students, and I'm just going to do it on the first one, I tell them just make a little substitution. So in this case, you're working with cosine of theta. So just let something like u be equal to the cosine of theta. Okay, so everywhere you see cosine of theta, replace it with u. So here I have cosine squared theta, which is basically cosine of theta squared. So I would say I have 2u squared plus, in this case, 3u, and then plus 1 equals 0. So from here, could I factor this and solve it using factoring? Yes, of course I could. So this guy is a prime number, and this guy is 1. So this is really easy to factor. This is going to be 2u and this is going to be u. We know that off the top. And we know that because this is positive 1 and all the signs are positive, the only possibility is that this would be 1 and this would be 1. So basically you would check this and say, okay, well 2u times u is 2u squared. The outer would be 2u, the inner would be u, so those combined together would give me the 3u, and the last would be 1 times 1, which is 1, so we're good to go. So you could have factored this the same way, using the same principles with the cosine of theta in there, but again, I use u there just to avoid the little roadblock of first factoring a trigonometric expression like this. So what I want to do now is, because u is cosine of theta, I just want to plug back in. So I'm going to say 2 times, everywhere there's a u, I'm plugging in a cosine of theta, then plus 1, and then times, you have your cosine of theta, plus 1, and this equals 0. So now that we've got this guy factored, let's set each factor equal to 0, and let's see if we can get a solution. So I'm going to start with this one. I'm going to say 2 times cosine of theta plus 1 equals 0. Let's subtract 1 away from each side of the equation. We're going to get 2 times cosine of theta is equal to negative 1. Divide both sides by 2, and I'm going to get that the cosine of theta is equal to negative 1/2. So you're going to see the same numbers pop up over and over again. You probably at this point know that the values for this in terms of degrees would be 120 degrees and 240 degrees. But I'll go to the unit circle in a moment and show you. So let me just erase this, kind of make this a little bit more neat. And I'll just say that cosine of theta is equal to negative 1/2. Let me just slide this over just a little bit. And I'll delete this from here. And I'm going to go down to the unit circle all at once. So let's do this side now. So we have cosine of theta. Basically, you're just subtracting 1 away from each side. So let's do the full thing. So plus 1 equals 0. Subtract 1 away from each side. You get cosine of theta is equal to negative 1. You probably know already this happens at 180 degrees or pi if you're thinking about radians. So let's move this up and say we have cosine of theta is equal to negative 1. So let's go to the unit circle real quick and get all of our solutions. Again, you can also do this using your calculator. You can do it with special triangles. There's so many ways to do it. But for the first two, they're very easy. I'm going to give you a final problem where you have to use your calculator. There's no other choice. Okay, so we'll see that. So let's go down to the unit circle. So again, if we're looking for cosine of theta is equal to negative 1/2, and then cosine of theta is equal to negative 1, where you're looking for an x value of negative 1/2. So that's going to happen here, again, at 120 degrees or 2 pi over 3 radians. And then also, remember, this guy would have a reference angle of 60 degrees. So you would want 240 degrees because that also has a reference angle of 60 degrees. So this is your negative 1/2 there. Again, 240 degrees or 4 pi over 3 radians. So let's write 120 degrees. And then I'm going to write 240 degrees out here. I'll put a little space here because I'm going to put this 180 degrees here for the negative 1, right? So negative 1 is your x value there. So let's put 180 degrees there. And let's just put the radians in there as well. Generally, you're going to give your answer based on the restriction you get, right? If they tell you the interval is between 0 and 360 degrees, you put degrees. If they tell you 0 to 2 pi, you put your radians. So let's go ahead and put, we have 2 pi over 3. We have pi, and then we have 4 pi over 3. So let's go ahead and copy this. We're going to need that. And we're back here. So let me just go ahead and paste this in. Bring this over here. So this is going to be our solution. Again, if you restrict the domain. So for this one, let's say that we restrict the domain from 0 degrees to 360 degrees. Okay, so basically in that interval. For this one, this is going to be if you restrict it from 0 to 2 pi, okay, in terms of radians. So based on what you get, that's how you're going to get your answer. If you're asked to get a general solution, remember, these guys are going to repeat, right? So with the sine or cosine, if you're working with one of those, the period, okay, is going to be 360 degrees or 2 pi in terms of radians. So just take this. If you wanted a general solution, so let's put general solution here. You would take these guys. So I'm going to say 120 degrees plus 360 degrees times n, where n is just any integer. You're just going to take all of them. So then 180 degrees plus 360 degrees times n. And then lastly, 240 degrees plus 360 degrees times n. Okay, let me close the set braces. Then for this one, remember 360 degrees is like 2 pi in terms of radians. So what I want to do here is say 2 pi over 3, and then plus, we'll have 2 pi times n. Okay, so n is any integer. Same thing, so pi plus 2 pi n, and then lastly 4 pi over 3 plus 2 pi n. So we have our general solution here, And then we have our solution where basically we're in an interval. You could say you're restricting the domain. All right, for the next one, let's look at 4 equals sine of beta plus 2 times sine squared beta plus 3. Again, if you have something squared and then something to the first power, I'm always thinking factoring, right? I'm always thinking ax squared plus bx plus c equals 0. So I'm going to write it like that. I'm going to first, let's go ahead and flip the sides. I want everything to be on the left side that I'm working with. So let's go ahead and say we have 2 times sine squared beta plus, let's say, sine of beta. I'm going to subtract 4 away from each side of the equation. So this would end up being basically -1 over here, because if I subtract 4 away from each side, this would be -1, and this equals 0. So now what I have here, I should be able to factor. So again, if you're struggling with this, if you just can't get past the mental roadblock, go ahead and take sine of beta and set that equal to a variable like u. But I think we can get past it, right? So I'm just going to put sine of beta here and sine of beta here to start. Now this 2 in front, that's a prime number, so I've got to stick that in one of these, so I'm just going to stick it here. So we have 2 times sine of beta times sine of beta, which will give me 2 times sine squared beta. Okay, so that works. Now we have alternating signs here. Let's think about this. We have a -1 as a final term, so it has to be 1 times 1, but we have to think about the signs there. Is it going to be plus here and minus here, or vice versa? Well, the outer here would be 2 times sine of beta, but it would be negative. And then the inner would be plus the sine of beta. So that's not going to work because the middle term's positive, okay? So that means I need a plus here and a minus here. So let's erase this. And now you see it works out, right? Because the outer would be 2 times sine of beta. And then the inner would be minus sine of beta. And so if I do the subtraction, I get my plus sine of beta, and then -1 times +1 is -1. So we have correctly factored this guy. Same thing. So 2 times sine of beta -1, I'm setting that equal to 0. Let's go ahead and solve it. Add 1 to each side of the equation. You get 2 times sine of beta is equal to 1. And I'm going to divide each part by 2 here. And basically I get that the sine of beta is equal to 1/2. So let's erase this. And you see these values so often, it's almost like you start dreaming about them. We know that this is going to be 30 degrees or 150 degrees. Again, if we're in that interval from 0 to 360 degrees, where you could say pi over 6 or 5 pi over 6 in terms of radians. So let me write this over here. So sine of beta equals 1/2. So right now I know beta is equal to, well, let me just do this in solution set notation. We know we have 30 degrees and we have 150 degrees. Okay, so far that's what we got. Let me put this in terms of radians also. So let's go pi over 6 and then 5 pi over 6. So what's going to be the result from over here? Let me draw a little line. We have the sine of beta plus 1 equals 0. Again, we're just going to subtract 1 away from each side. So the sine of beta is equal to -1. And again, if you know your unit circle, this is basically going to give us 270 degrees or 3 pi over 2. So let's get rid of this. And let's put 270 degrees. And then over here, let's put 3 pi over 2. Let me just erase this real quick. And let me just drag this out of the way. So we'll put this over here. So let's put or. And then let's come down here. And again, the more you reference the unit circle, the more you work with it, the more you memorize it. Again, we were looking for sine of beta to be equal to 1/2. So that's going to be here. You're looking for your y value, so 30 degrees or pi over 6. And then if I go in quadrant 2 where sine is positive, again, what angle is going to have a reference angle of 30 degrees? 150 degrees. So it's going to be here. Okay, it's 150 degrees or 5 pi over 6. Then if you're looking for a y value of -1, it's going to be at 270 degrees or here, or again, 3 pi over 2 in terms of radians. Okay, so let's talk about the general solution. This might not be obvious, but when you look at these, sometimes they're going to have this pattern. I know when we work with sine or cosine, they repeat every 360 degrees. But if you notice this one, if you started, let's say you went through and you say, okay, well, 30 degrees plus 360 degrees is 390 degrees. Then 150 degrees plus 360 degrees is 510 degrees. And then 270 degrees plus 360 degrees is 630 degrees. So I want you to notice that everything that I have here is just differing by 120 degrees. So if I start here and go here, I added 120 degrees, I added 120 degrees, I added 120 degrees, so on and so forth. For a general solution, in this particular case, I can say 30 degrees, okay, plus, I know the period of sine is 360 degrees, but because of this, I can say 120 degrees times n. So 30 degrees plus 120 degrees times n, this would be a simpler way to write this. And then for this guy, if you want to put this in terms of radians, let's go ahead and just say that you have pi over 6. Plus, you're going to do 120 degrees in terms of radians, so that's 2 pi over 3. So 2 pi over 3, and then times that. Okay, so let's close that up. So this would be our general solution, and then this is if we had a domain restriction. So let's say from 0 to 360 degrees. And then here, let's do from 0 to 2 pi. All right, let's look at one that's much more challenging. So here, we're not going to be able to use our fancy unit circle. I think we can on one part, but on the other we can't. So we have tangent squared beta plus tangent of beta minus 2 equals 0. So same deal, I'm going to be able to factor this, and I'm just going to set this up. It's already in line for me the way I want it. So I'm just going to put the tangent of beta and the tangent of beta. So I basically need a positive 1 and a negative 2. So how am I going to get that? Well, basically I want to do positive 2 and negative 1. So this guy is factored, pretty easy to do that. Let's go ahead and start with the easier one. So let me start with the tangent of beta minus 1 equals 0. So we'll say the tangent of beta, if I add 1 to each side, would be equal to 1. So where's the tangent of beta equal to 1? You might remember from your special triangles that one solution here would be 45 degrees. Remember, tangent is positive in quadrants 1 and 3. Remember all students take calculus. So it's positive in quadrants 1 and 3. Okay, so I need to find the quadrant 3 solution. So I want the angle in quadrant 3 with a 45 degree reference angle. So I can go ahead and do 180 degrees plus 45 degrees, which is going to give me 225 degrees. So let me put 225 degrees to finish that up, and then I can erase it. So let's put beta is equal to 45 degrees or 225 degrees. In terms of radians, you could write it like this. You could put pi over 4, and then you could do 5 pi over 4. So that takes care of this part. Now over here, this is where we're going to struggle a little bit. So we have the tangent of beta plus 2. We're going to set that equal to 0. So let's go down here, get a lot of room. We'll come back up. So the tangent of beta plus 2 is equal to 0. Let me subtract 2 away from each side of the equation. I get the tangent of beta is equal to negative 2. So there's nothing you can pull from special triangles or the unit circle where you're going to figure this out, okay? So what I would do here is go through and basically use your inverse tangent function on your calculator, okay? Go ahead and use this guy, okay? And I'm going to use positive 2, not negative 2. If you punch this up, you're going to get 63 point, and I'm going to round this, let's say 4, 3. So this is in terms of degrees. So now what this is telling me is that the reference angle with wherever I need to go is going to be 63.43 degrees. Now tangent of beta here is negative. Where is tangent negative? It's negative in quadrants 2 and 4. So I'm looking for a solution in quadrants 2 and in quadrants 4. And what I want is the angle with a reference angle of 63.43 degrees. So in quadrant 2, I would do 180 degrees minus 63.43 degrees, which I'll say is 116.57. So let's go ahead and write this as 116.57 degrees. And then in quadrant 4, I would do 360 degrees minus this 63.43 degrees. And that would give me 296. Let me write this down. So 296.57 degrees. So let's erase all of this. We don't need it anymore. And let's just bring this up here. And I'm going to combine all of this for one solution. So let me get this over here. And let me come up here. And I'm basically going to say, and let me kind of drag this over here. So I'm going to do one for degrees and one for radians. So beta could be 45 degrees, 225 degrees. You could have 116.57 degrees. And this is an approximation. So maybe you want to notate that this is approximately here. And then this is an approximation also. So 296.57 degrees. And then in terms of radians, if you wanted to convert this over, again, for each of these, you would multiply by, you have degrees here. So you want degrees down here. And then you want pi up here. So you would basically say that the degrees are going to cancel. So let me just show that real quick. 116.57 divided by 180. And then I'm just going to multiply it by pi. And I'm just going to round this off and say it's about 2.034. So let me slide this down. And I'll just say it's about 2.034. So let's get rid of this one. And let's do this one. So let's move this up. And basically we're going to multiply by, again, you want pi over 180 degrees. We know that the degrees here are going to cancel. And basically, I'm doing the same thing on my calculator. 296.57 divided by 180, then times pi. So let's just go ahead and say this is going to be 5.176. So 5.176. And again, you just want to show some way like, hey, this is an approximation. So I'll just put approximately like this, just showing that this is not an exact value. Now remember, if you're working with tangent, the period is 180 degrees or it's pi radians. Okay, so this would be for, in the case of from 0 to 360 in terms of degrees, and I made that terribly. Okay, so 360 degrees. And then this would be basically from 0, let me put my degree symbol there, 0 to 2 pi. And then for the general solution, I'm going to take 45 degrees. So let's go ahead and say 45 degrees. Plus, I'm going to do 180 degrees times n. And then I have another guy here, so I'm going to do 116.57 degrees plus 180 degrees times n. So again, this is an approximation. This is an approximation. It is not an exact value. Depending on your teacher, you might have to show that in some way. So that's why I put this here and this here and this here and this here. That's just my way of notating. This isn't standard. This is my way of notating that, hey, this is an approximation. It's not an exact value. So then down here, for this guy, I would start with pi over 4 and then plus the pi times n. And then for this one, I would take my 2.034 and then plus my pi n. Okay, like this. Now again, if you want to just notate that this is an approximation and this is an approximation, just to let your teacher fully know that you're aware that this is an approximation and not an exact value. All right, let's take a look at one more problem. So somewhere in your textbook, they're going to tell you that you don't want to divide both sides of an equation by a trigonometric function, such as the cosine of beta. So when you do this, you could potentially remove some of your solutions. These are going to be solutions that make the divisor 0. So what I'm going to do is solve this in two different ways, and I'll show you how this can cause problems. So the first way is the correct way, and that's with factoring. So if you have the cosine of beta times the cotangent of beta, and this equals the cosine of beta, you could subtract the cosine of beta away from each side of the equation. So over here, this would cancel, and you'll have 0. So on the left, you would have the cosine of beta, then times the cotangent of beta, and then minus this cosine of beta. And what I'm going to do, because we're going to factor this out, let me put times 1 so nobody gets lost. And I'm going to set this equal to 0. Let me actually get rid of this because we're going to come back up and use that in a moment. So let me slide down here just a little bit. And I'm just going to factor out the cosine of beta. So this right here is going to get pulled out in front of some parentheses. So you have the cosine of beta times the quantity. Inside, you would have the cotangent of beta. And then minus, if you pull this out, you would have your 1, and then close that down, and this equals 0. So we're now going to solve this using the zero product property, or you can call it the zero factor property. So for that, I'm going to take the cosine of beta and set that equal to 0. Then I'll say or. I'm going to take this other factor, so the cotangent of beta, minus 1, and set that equal to 0. Well, for this one, you could add 1 to both sides. So the cotangent of beta would be equal to 1. And we know that the tangent of beta is equal to 1 over the cotangent of beta. So the tangent of beta here would be 1 over 1, which is 1. So let me write this as the tangent of beta equals 1. So the first one is the cosine of beta equals 0. So I'm looking on the unit circle for an x-coordinate of 0. So that's going to occur right there at pi over 2 or 90 degrees. And then right there at 3 pi over 2 or 270 degrees. Now for the tangent of beta equals 1, we've seen this several times already. We know that in the first quadrant, this is going to be pi over 4. Again, if you skip the other problems, you could just do the inverse tangent function with 1 as the argument. You'll get pi over 4 or 45 degrees. You could also think about this with the definition of tangent. So you could say that the tangent of beta is equal to the sine of beta over the cosine of beta. And in this case, if you replace beta with that angle, which is pi over 4, you can go to the unit circle and actually see why we're getting a value of 1, and that's because we have the same non-zero number divided by itself. The sine value is square root of 2 over 2. The cosine value is square root of 2 over 2. So square root of 2 over 2 divided by square root of 2 over 2 will give you 1. And then the period for tangent is pi. So if I add pi radians, or 180 degrees, that's going to give me my solution that's in quadrant 3. So that's going to be at 5 pi over 4, and the tangent of 5 pi over 4, again, you would have the same non-zero number divided by itself, and so you would get 1. So let me get rid of this, and let me highlight this over here as 5 pi over 4, or 225 degrees, and I'll get rid of this, and this, and this. So if you wanted to write out your solution, you could say that beta is equal to, let's start with pi over 4, and then let's go to pi over 2, and then let's go to 5 pi over 4, and then let's go to 3 pi over 2. If you want to work with degrees, we could say that this is 45 degrees, this is 90 degrees, this is 225 degrees, and then lastly 270 degrees. Okay, let me grab this real quick, and let me come back up here and paste this in here. And I'm just going to show you real quick that these solutions all work, just so that when we get to the next part, you're not lost in terms of whether we did it correctly or not. So the first solution was pi over 4. So let's plug that in there, and there, and there. And let me make that a little bit better there. Let me slide this out of the way so we can fit this. We know that the cotangent of pi over 4 is 1, and the cosine of pi over 4 is square root of 2 over 2. So this would be the square root of 2 over 2 times 1 is equal to the square root of 2 over 2. So that is a valid solution. Now, similarly, if you do 5 pi over 4, the only thing that's going to change is the cosine of 5 pi over 4, that's going to be a negative square root of 2 over 2. So if I did 5 pi over 4, 5 pi over 4, and 5 pi over 4, this would be negative square root of 2 over 2 times 1 equals negative square root of 2 over 2. So that one's going to work as well, because you get the negative of the square root of 2 over 2 equals the negative of the square root of 2 over 2. Now, the other ones are going to make the cosine of beta equal to 0. So whether you did pi over 2 or 3 pi over 2, when you plug that in, let me just do pi over 2, you're going to get 0 equals 0. And let me make that a little bit better there. So cosine of pi over 2 is 0. Cotangent of pi over 2 is actually also 0. So you would get 0 is equal to, over here, cosine of pi over 2 is 0. So this one would work, and so would this one. It's the same thing. So you can see these solutions work in our interval. So from 0 and including 0 going out to 2 pi is excluded. And then for this one, you would have from 0 degrees where that's included, going out to 360 degrees where that's excluded. Okay, let me get rid of this. And let me show you what can happen if you solve this in a different way. So let's say instead of factoring, I decided I was going to divide both sides of the equation by the cosine of beta. So let's divide this side by cosine of beta, and let's divide this side by cosine of beta. And you're going to see a problem happen. So this would cancel with this, and you'd have the cotangent of beta is equal to, well, this would cancel with this, and I have a 1. So it equals 1. Okay, well, we know this turns into the tangent of beta equals 1, and we know we get this solution right here of pi over 4, and we get this solution right here, which is 5 pi over 4. But what happened to these solutions right here of pi over 2 and 3 pi over 2? Well, those are the solutions that make this divisor 0. Cosine of pi over 2 is 0. Cosine of 3 pi over 2 is 0. So that's what's going on. You're going to potentially remove solutions if you use this strategy. So what we want to do is stick to factoring when we try to solve this type of problem, because you're not going to run into these types of issues. So I just want to note real quick, for those of you that are interested, you can look at this problem on Desmos. What you would want to do is go back to the fact that you have the cosine of beta, I'm just going to call it the cosine of x, times the cotangent of x is equal to the cosine of x. Now what you're going to end up doing is graphing this guy on the left and this guy on the right separately. So the graph in red is y equals the cosine of x times the cotangent of x, and the graph in green is y equals the cosine of x. So if you want to solve it this way, you're looking for the points of intersection between those two graphs. So you're basically asking the question, for which x values are the y values going to be the same? Those are going to satisfy the equation. So the ones we found pi over 4, we found pi over 2, we found 5 pi over 4, and then we found 3 pi over 2. So you can continue with that if you want. This is something you can look at on Desmos on your own if you want a visual representation of what's going on. In this lesson, we want to talk about solving trigonometric equations using square roots, squaring, and identities. All right, so let's go ahead and start off with 4 times sine squared beta minus 1 equals 0. So just like we've been doing before, we're going to add 1 to both sides of the equation. We're going to have 4 times sine squared beta is equal to 1, okay? So what I want to do now, remember you're always trying to isolate your trigonometric expression. So I want sine of beta by itself. So what I'm going to do here is just divide both sides by 4, okay? And so that's going to give me the sine squared beta is equal to 1/4, okay? Let me scroll down just a little bit and get some room. So now, because this guy is squared, I want to take the square root of each side. Remember how this works. If I take the square root of the left, on the right, I want to go plus or minus, right, to account for the positive or the negative. So I'm going to say that the sine of beta is equal to plus or minus the square root of 1/4, okay? If you simplify this, you'll say the sine of beta is equal to, you'll go plus or minus, the square root of 1 is 1, and the square root of 4 is 2. So you can basically say this is 1/2, okay? So let me actually erase all of this, and let's come up to the top and just paste this back in here. So we know this gives us 2 scenarios, right? So I want to split this up and say the sine of beta is equal to 1/2, or the sine of beta is equal to the negative of 1/2. So let me erase this now, okay? So we have our 2 guys there. So basically what I'd want to do is go to my unit circle. I know at this point a lot of you already have it memorized, but some don't. So let's go down and let's look for where the sine of beta is equal to 1/2, and then also where the sine of beta is equal to negative 1/2. So basically you're looking for your y-coordinate to be 1/2 or negative 1/2. So that's going to happen here, okay? That's also going to happen as we go around. It's going to happen here. As we go around, it's going to happen here. And then as we go around, it's also going to happen here, okay? So notice everywhere where I circled has a 30-degree reference angle, right? So basically, it's going to be, if you want to put this in terms of radians or degrees, we'll just do both. So 30 degrees. Then you have 150 degrees. You also have your 210 degrees. And then you have your 330 degrees. Okay, so that's in terms of degrees. And then in terms of radians, you would have your pi over 6, okay? You would have your 5 pi over 6. You would have your 7 pi over 6. And then lastly, you would have your 11 pi, okay, over 6. So these would be your solutions if you said between 0 and 360 degrees, or also if you said between 0 and 2 pi in terms of radians. So let's just cut this away. I'm just going to cut this, come back up here and paste this in, okay? So these are going to be, again, our solutions. Let me just erase this nonsense here. These are going to be our solutions for basically if you restricted this over an interval. Again, you have from 0 degrees to 360 degrees. That's this guy right here. And then this guy right here would be from 0 to 2 pi, okay? So sometimes they ask you this question to solve over a specific interval. And then other times they'll say, hey, what's the general solution? So if we want the general solution, let's just put this right here really quickly. Remember, when you work with sine, the period is going to be 360 degrees. But what you notice here is that as you jump here from 30 degrees to 210 degrees, you're increasing by 180 degrees, okay? So I would start this by saying I have 30 degrees plus 180 degrees times some integer n. And then you'd have 150 degrees, so 150 degrees plus this 180 degrees, okay, times n, because again, if you look at 150 degrees and 330 degrees, those are different by 180 degrees, okay? And what's causing this, if we go back to the unit circle, if I circle this one again, you'll notice that these guys are across from each other. This is 180 degrees, right? So basically, these are across from each other, and these are across from each other, okay? So you can basically say that you start with 30 degrees, and you add 180 degrees to get your next solution. Then you add 180 degrees again, you get to the next solution, so on and so forth. If you start with 150 degrees, you add 180 degrees to get your next solution, then 180 degrees again, so on and so forth. Okay, if you wanted to put this again in terms of radians, we're going to use the same concept. Here I'm going to go pi over 6, so basically your 30 degrees. Then plus 180 degrees in terms of radians is going to be pi, okay? So you're just going to do pi times n. And then for 150 degrees, this is going to be 5 pi over 6, so 5 pi over 6. And then I'm just going to go plus my pi times n, okay? So here's all the solutions that you could possibly want. You have your degrees across that interval from 0 degrees to 360 degrees, and then you have your radians across that interval from 0 to 2 pi, and then you have your general solutions. So they're just basically, if they didn't ask you to solve over an interval, this is how you'd want to list this for degrees and then for radians. All right, let's take a look at another example. So here's one where we're going to need to use some identities. So we have the negative of cosine squared beta minus 2 times sine of beta is equal to negative 2. So notice that you have sine here and then also cosine here, and cosine specifically is squared, okay? So what you're meant to think about, if we go back to our worksheet or our little handout on the identities, if you go to the Pythagorean identities, remember cosine squared theta is the same as 1 minus sine squared theta, okay? So you want to look for possibilities there where you can substitute things in. So remember the negative here. This is a big deal. If you have a negative there, you're putting a negative. Put this in parentheses, what I'm going to do, because the negative's got to get distributed to everything. So I'm going to go 1 minus my sine squared beta, okay? Again, that's in parentheses. Then minus your 2 times your sine of beta is equal to negative 2, okay? Distribute the negative to everything. So I'll say negative 1 and then plus sine squared beta. Then minus 2 times sine of beta is equal to negative 2. Okay, so from here, we already know what to do. We want to end up with sine of beta equals some number, and then we want to solve, right? So I'm going to tell you in advance this is factorable. If you have something that is quadratic in form, if it's not factorable, you can use the quadratic formula, okay? But here we're going to be able to factor. So what I'm going to do is I'm going to add 2 to both sides of the equation, and I'm just going to rearrange things. I want the squared term all the way to the left, so I'm just going to say that I have sine squared beta, and then this is gone. I'm going to put 0 here. Okay, over here, I'm going to put minus 2 times the sine of beta, and then if I have negative 1 plus 2, that's positive 1. Okay, so this equals 0, and the idea here is that I can factor the left side. Okay, so I can factor this. Again, if it's a roadblock for you when you're trying to factor these guys, go ahead and take something like u, okay, and say sine of beta equals u, and then it's just like if you were trying to factor u squared minus 2u plus 1. Okay, if that was equal to 0, you could solve that in a breeze, right? It's just a roadblock because we're now dealing with trigonometry. So how could we factor this guy right here? And again, if it's troubling you, just look at this one. Well, first off, if I had sine squared beta, and there's nothing out here, there's basically a 1, well, I'm going to have the sine of beta times the sine of beta. Okay, so that's my first term in each case. Now, for this part right here, again, you're just looking at the negative 2 and the positive 1. Okay, so I need two numbers that are going to multiply together to give me positive 1, but sum to negative 2. Well, that's going to be negative 1 and negative 1. Okay, so let's go ahead and get rid of this. And basically, we could write this, okay, as the sine of beta minus 1 quantity squared. Okay, so this equals 0. And the reason I write it like this is you can write it like this or this. Remember, this is basically from special factoring. When you think about this, it's really only going to be one of these guys that we have to set equal to 0, right? Because you have a duplicate solution. So basically, all I want to do here is just, again, take one of these and say sine of beta minus 1 is equal to 0. I'm going to go ahead and add 1 to both sides and just say the sine of beta is equal to 1. Okay, now this is going to be really easy to solve for us. Where does the sine of beta equal 1? Well, if we're looking for the sine of beta equals 1, well, again, where's the y-coordinate 1? Well, right here, right? So at 90 degrees or pi over 2 in terms of radians. And that's basically the only place there. So your general solution would just be you rotating around another 360 degrees before you get there, okay? So let me go back up. So let's just put our solution here. So again, if we're in the interval, if they give you degrees, you want to answer in degrees. So if they say over the interval, you have 0 degrees and then to 360 degrees. Again, if you get this, then your answer should be in degrees and you'd want to put 90 degrees here, okay? If you got an answer or if you got a test question where, let's say it was with radians, so let's say they said 0 to 2 pi like this, okay? Then now you want to give your answer in radians. So you could say beta is equal to pi over 2, or you could do the solution set notation. Just ask your teacher what they want. Okay, so I'm just going to do this. So pi over 2, okay? So that's my solution basically in these intervals. Now, again, a general solution is where we keep thinking about when we just keep rotating around and around and around. So basically your general solution, if it's in terms of degrees, well, it would be 90 degrees plus another full rotation is 360 degrees times some integer n, okay? And then for the radians, you just use this pi over 2, and then plus, again, one full rotation in terms of radians is 2 pi, so you would do 2 pi and then times some integer n, okay? So this is your general solution here. Sometimes they ask for that. And then these are your solutions if you have a specified interval. Sometimes they ask for that. Okay, so let's look at a very, I would say challenging, but a very tedious type of problem now. This one involves squaring, and you'll recall from basic algebra, if you square both sides of an equation, you lose information. And so you have to basically check your solutions in the original equation, right? You sometimes get these extraneous solutions, and so they're not going to work as solutions to the original equation, okay? So we're going to see that here, and we're going to see that it just takes a long time to go through everything. So we have the negative of cosine theta is equal to the square root of 3 times the sine of theta. Okay, so the first thing I'm going to do is square both sides, okay, because I want to get rid of this radical, and also I have cosine and sine, so I'm thinking Pythagorean identity, okay? So I'm going to square both sides. So let me write this as the negative of cosine of theta, okay? This is going to be squared. This equals the square root of 3 times the sine of theta. This is going to be squared, okay? So the negative is going to go away. Negative squared is just going to be a positive, right? Negative 1 times negative 1 is positive 1. Then cosine of theta squared, we could just say this is cosine squared theta like this. Over here, the square root of 3 being squared is 3. Sine of theta being squared is just sine squared theta, okay? So at this point, we know that cosine squared theta is 1 minus sine squared theta, okay? So let's just go ahead and make that substitution. I'll say this is 1 minus sine squared theta is equal to 3 times sine squared theta, okay? So let's scroll down and get some room going. All right, I'm just going to subtract 3 times sine squared theta from both sides of the equation, and this is going to cancel, and I'm just going to put 0 here. So I'm going to have 1 minus, remember, you can treat this as a negative 1. So negative 1 minus 3, or negative 1 plus negative 3, however you want to think about this. This is going to be minus 4. Okay, so basically negative 4 times sine squared theta is equal to 0. Okay, so how are we going to solve this? I want you to think back again to basic algebra. Okay, this is where your skills really come into play. Let's say it's something like a squared minus b squared. How would you factor this? Remember, this is the difference of squares. So it's a plus b, okay, that quantity times a minus b, that quantity. Well, here you have the difference of squares, right? I could write this out and say that this is 1 squared minus, you could do 2 times the sine of theta, okay, quantity squared like this, and this equals 0, okay? So now it's apparent, or it's very clear, that this is the difference of squares. Sometimes you have to rewrite things like that. So this would be 1 plus 2 times the sine of theta times 1 minus 2 times the sine of theta, okay? And we'll set this equal to 0. So basically, I'm going to take each one of these guys and set it equal to 0. So I would have 1 plus 2 times the sine of theta is equal to 0. Or you'd have 1 minus 2 times the sine of theta is equal to 0. Let's go ahead and solve. They're very easy to solve. I subtract away 1 from each side over here, and over here, and over here. And this is going to cancel, and this is going to cancel, okay? So over here I have 2 times the sine of theta is equal to negative 1. Over here I have, and let me put the or, I have negative 2 times the sine of theta is equal to negative 1, okay? So basically at this point, I'm just going to divide this by 2, okay, and this by 2, and then this by 2, or this is negative 2 over here, and this by negative 2. Okay, so this cancels, and I have sine of theta is equal to the negative 1/2. Then or over here, this is going to cancel, right? And you have negative divided by negative, so that's positive. So you get the sine of theta is equal to 1/2, right? So you can condense this down and say basically you have plus or minus 1/2. Okay, so let's get rid of this. And let's just copy this real quick. Let's go to a fresh sheet. So we have a lot of room to work, because the problem here is you're going to get all these solutions, okay? So if the sine of theta is 1/2, or it's negative 1/2, remember, we already went through this. So let me write this again. So sine of theta is 1/2, or sine of theta is negative 1/2. Basically, you would have a 30-degree reference angle in each case, right? So you would have here, and then basically you go around, you'd have here, and then you go around and you would have right here, and then you go around and you would have right here, okay? So we already know this because we saw a problem with this earlier, but basically 30 degrees, 150 degrees, 210 degrees, and 330 degrees, okay? So let me write this down. So we have our 30 degrees, we have our 150 degrees, we have our 210 degrees, and then we have our 330 degrees, okay? And I'll write it in radians when we finish up, so let me just keep this in degrees for now. Let me cut this away, and let me just paste this in right here, okay? Let me get rid of all this nonsense. Now, when we square both sides of an equation, the solutions here that we get are proposed solutions. So we have to get our original equation going so we can check it. So negative cosine of theta, okay, is equal to the square root of 3 times the sine of theta. Okay, so we're just going to use degrees. You can use radians, it doesn't matter. You're going to plug in for theta, okay? So basically, if I plugged in 30 degrees here and 30 degrees here, what would we get? Well, again, I could go back and forth between the unit circle, but a lot of you already know that the sine of 30 degrees is a half, okay? So this is going to be 1/2. So this would give me the square root of 3 over 2. So let's just write that as the square root of 3 over 2. Okay, over here, I'd have the negative of cosine of 30 degrees. Well, the cosine of 30 degrees, you know, is a positive number, right? Because 30 degrees is in quadrant 1. All of these guys are going to be positive in quadrant 1, right? So there's no way this can be true because this is the negative of a positive number, okay? So you can go ahead and mark this out. The actual answer here is square root of 3 over 2, right? But it's the negative of that. So it's the negative of the square root of 3 over 2 is equal to the square root of 3 over 2, so that's false, right? So that solution does not work. Okay, for the next one, let me erase this and set this back up. So we had the cosine, or the negative of the cosine of theta, is equal to, we had the square root of 3 times the sine of theta. So we know that the sine of, if I put in 150 degrees here, we know the sine of 150 degrees is basically a half, right? Because the sine of 30 degrees is a half, the sine of 150 degrees, because sine is positive in quadrant 2, 150 degrees has a 30-degree reference angle, so this is a half as well, right? So this is basically going to be the square root of 3 over 2, okay? Over here, if you think about the cosine of 150 degrees, remember cosine is negative in quadrant 2. Okay, so this will save you a little bit of work. You'd have the negative of a negative, which is positive, so you know this is probably going to work, right? So the cosine of 150 degrees, we know that this guy is going to be the negative of the square root of 3 over 2. Okay, but you have the negative of the negative, so be really careful. So the negative of the square root of 3 over 2. So if I apply the negative, I basically would have the square root of 3 over 2 is equal to the square root of 3 over 2. Okay, so this one checks out. So 150 degrees is a valid solution. Then for 210 degrees, let's go ahead and set this back up. And I probably shouldn't erase this each time, but it's the negative of the cosine of theta is equal to the square root of 3 times the sine of theta. So 210 degrees, if you put this in here, okay, and you put this in here, again, we know that the reference angle is 30 degrees, right? So what is the sine of 30 degrees? Well, it's going to be 1/2, but we're in quadrant 3 now, so we know this is negative. So basically, this is negative 1/2. So this would be the square root of 3 times negative 1/2, so square root of 3 over 2, and this is negative, okay? So over here, 210, again, this many degrees, I know that I have a reference angle of 30 degrees, so the cosine of 30 degrees is square root of 3 over 2, and because this guy is in quadrant 3, cosine is negative, so this is the negative of the square root of 3 over 2, so this isn't going to work out, right? Because again, if I apply the negative, this becomes positive. So again, we have one that doesn't work. So this one doesn't work. And then for 330 degrees, let me just do this one last one. So the negative of cosine of, let's just go ahead and say 330 degrees, is equal to, you have the square root of 3 times your sine of 330 degrees. Again, I've got a 30-degree reference angle, and I'm in quadrant 4. So I know this is negative 1/2, right? So you might as well just put negative square root of 3 over 2, okay, like this, and I'll just put this out here. Okay, so over here, again, I have a 30-degree reference angle, but cosine is positive, okay, in quadrant 4. So I would say square root of 3 over 2. So square root of 3 over 2, but it's the negative of that because I've got this negative hanging out. So these guys are equal, so this one does work out, okay? So your two valid solutions here are 150 degrees or 330 degrees, okay, in terms of degrees. And then if you're working with radians, it's 5 pi over 6 or then 11 pi over 6. So let's go ahead and write our solution here. We'll say from the interval, if you're in this interval 0 degrees and then 360 degrees, we'll say the solution set is basically 150 degrees, okay, and then 330 degrees only, okay, so just those two guys. And then if I'm in this interval from 0 to 2 pi, okay, if they give it to you like this, always answer based on what they give you as the interval, okay? If they don't give you anything, then you can just ask your teacher like, hey, what do you want this in? So basically, at this point, I want to do my radians, so I'll go ahead and say that this is 5 pi over 6, and then 11 pi over 6. Let me close that down. And then again, if you want a general solution, you want to realize here that you can just add 180 degrees each time. Again, I know the period for sine is 360 degrees, but you have to pay attention to this type of stuff if you're writing a general solution. So the general solution here would be, let's go ahead and say 150 degrees plus 180 degrees times n. Okay, so you don't want to do 360 degrees there because, again, if I add 180 degrees, I get to 330 degrees. Then if I add 180 degrees to that, I'm going to be at 150 degrees plus 360 degrees, which is 510 degrees, so on and so forth. Okay, and then in terms of radians, I'm going to go ahead and say that it's 5 pi over 6 plus 180 degrees is going to be pi radians and then times that. Okay, so these are your general solutions, and then these are your solutions if you're given a specific interval to solve over. Just get with your teacher in terms of what you need to do. In this lesson, we want to talk about solving trigonometric equations with half angles. All right, so let's start off with a very easy example. So we have the sine of beta over 2 is equal to the square root of 2 minus the sine of beta over 2. We have a little domain restriction, or you could say you're solving over an interval. In this case, it's from 0 to 2 pi, with 0 being included. Okay, now I want to make something perfectly clear. You are solving for beta. Okay, so you want to plug something in here for beta. So basically here and here, and you want the result of this to be true. Okay, you are not in the end solving for beta over 2, but we need to use beta over 2 in order to get a solution. Okay, so what we're going to have to do, and let me write this down here, I'll show you. We need to basically change this up just a little bit, and I'll explain why. So let me rewrite this real fast. I'm going to say that I have the sine of beta over 2 is equal to the square root of 2 minus the sine of beta over 2. Okay, so the first thing I'd want to do is get that trigonometric expression by itself. And in order to do that, I'm just going to add the sine of beta over 2 to both sides of the equation. Okay, so that's how I'm going to get things started. So let me scroll down just a little bit here, get some room going. And I'm just going to show this cancels over here. So sine of beta over 2 plus sine of beta over 2 is 2 times the sine of beta over 2. And this equals now the square root of 2. Okay, if I want to isolate this completely, I'm multiplying this by 2. Okay, so I can just divide both sides by 2, and then I'll take care of that. So I'll divide this side by 2 and this side by 2. And basically, this is going to cancel with this. Okay, so that's gone. And I've isolated the sine, and let me make that a little bit better. So it's the sine of beta over 2. So that's on my left side. On the right side, I have the square root of 2 over 2. Okay, so let's pause for a minute. I'm actually going to erase all this. And let's think about what we have. We have this right here, which is beta over 2. And we have the sine of that guy. And we're saying that it's equal to the square root of 2 over 2. So before we start thinking about how we're going to solve this, let's first modify our little domain to work with what we're working with here. We're working with beta over 2. So I'm going to write this as an inequality. I'm going to say that 0 is less than or equal to. I'm going to do this beta guy here, which is less than 2 pi. Okay, because that's what we're initially working with. Again, this is for beta. So now we have beta over 2, so we divide everything by 2 here, okay, to consider the interval here. So this is just going to be 0. This will be beta over 2, and this is just going to be pi. Okay, so essentially what I'm looking for here is I'm looking for where beta over 2, sine of that guy, would be square root of 2 over 2. Now, in this particular case, if you think about square root of 2 over 2 in terms of sine, if you go to your unit circle, you can see in quadrant 1, you have square root of 2 over 2 here with pi over 4 in terms of radians, or 45 degrees with degrees. And then you would want a 45-degree reference angle in quadrant 2, okay? So in terms of degrees, that's going to be 135 degrees, or 3 pi over 4 in terms of radians, right? So right here, okay? And you can see this right here. Okay, so that's pretty obvious, and you can see that that falls in line with our interval for beta over 2 because it's from 0 to pi, okay? So we're going to take pi over 4 and 3 pi over 4. So I'm going to say that the sine of pi over 4 is equal to the square root of 2 over 2, and also that the sine of 3 pi over 4, okay, is equal to the square root of 2 over 2. Okay, so what I want to think about here, now that I have everything set up, remember, you can set these guys equal to each other because I know that the sine of pi over 4 is equal to the square root of 2 over 2. And I know that beta over 2, sine of that guy, is equal to the square root of 2 over 2. So what I can do here is set up a little equation so that I can solve for beta, right? So let me do this over here. I'm going to say that beta over 2 is going to be equal to pi over 4. Because again, sine of this guy produces this, and sine of this guy produces this. So I can set these two equal to each other in order to get a solution for beta. Okay, so that's why that's going on. Okay, so let's scroll down just a little bit to get some room. I'm going to put or here. I'm going to do the same thing with this. So beta over 2 is equal to the 3 pi over 4. okay? And all I need to do here, it's very simple to get a solution. I'm just going to end up multiplying both sides by 2, okay? So this is basically going to be what? This is going to cancel. I'll have beta is equal to, the 2 would cancel the 4 and give me a 2 down here, so pi over 2. And then over here, basically I'm multiplying both sides by 2. And so this is going to cancel, and this is going to cancel, give me 2 here. So we'll say, or beta is equal to my 3 pi over 2, okay? So these are our two solutions in terms of radians, and they're within our domain or our restrictions. So I'm going to do this in solution set notation. So I'm just going to put pi over 2, and then comma 3 pi over 2, okay? So we're not asked for the general solution here, so we don't need to worry about that. If you were asked for the general solution, remember your period here is different because you're dividing by 2. So basically the period here is 4 pi, okay, not 2 pi. Okay, so you got to remember that. All right, so one thing I want you to do is pause the video, go ahead and plug pi over 2 in for beta in each case, and verify that basically these solutions do work. You can just do one of them. I'm going to just say, trust me that they both work, but just pause the video and see that for yourself, that if you plug in pi over 2 right here, okay, so you have pi over 2 divided by 2, and right here, pi over 2 divided by 2, that basically you would get a true statement. The left side would be equal to the right side. Okay. Let's take a look at another example. So this one is slightly more complex. Not more complex, but more tedious because you do need to use an identity, and then there's some squaring involved. So we have the negative cosine of theta is equal to negative 2 plus 3 times the sine of theta over 2. Again, when you think about these things, if you end up with cosine and then sine, you're going to be thinking about an identity, right? So if I think about sine of theta over 2, if I go back to my handout on the identities, and we come down here, let's go all the way down to where we get to the half angle identities, and it was the last one we talked about. So here's the one for sine. So you have sine of a over 2. In our case, we're working with theta. So let's say sine of theta over 2 is equal to plus or minus your square root of 1 minus the cosine of theta over 2. Okay, so let's go back and let's just make a little replacement. Okay, so I'm going to put the negative of cosine of theta is equal to, I'm going to have negative 2. And then I'm going to have plus, you've got your 3 here that's multiplying this. So keep in mind that basically you have that plus or minus. I'm going to put this in front. So I'm going to do plus or minus like this, and then the 3, and then times that little guy, which was the square root of 1 minus the cosine of theta, and this was over 2. Okay, so all I did was I plugged in for sine of theta over 2, just using the half angle identity. Okay, that's all I did. Now, what I want to do here, remember, if you have a radical somewhere, you're going to end up having to square, okay? And in order to do that, you first want to isolate this guy, okay? So what I would do here is I would first add 2 to both sides, okay? And let's scroll down just a little bit. So I'm just going to say that I have 2 minus the cosine of theta is equal to, this is canceled over here, so I have plus or minus 3 times the square root of 1 minus cosine of theta over 2. Now I can square both sides, okay? So I can get rid of this radical. So I'm going to square this side, and I'm going to square this side, okay? When you square the plus or minus, you don't have to worry about it because basically you can think about this as negative 1 being squared, that's going to be positive 1, and a positive, you square it, it's still positive, okay? So you can basically forget about that. So over here, I'm going to use my special product formula and say it's the first one squared, so 2 squared is 4. And then minus, it's 2 times the first guy times the second guy. So 2 times 2 is 4. And then times cosine of theta, and then plus the last guy squared, so this is just cosine squared theta, okay? And we'll rearrange this in a moment. I know this is not how we usually write this. We'll put equals. Again, don't worry about the plus or minus, that's gone. 3 squared is going to be 9, and then it's multiplied by this guy right here squared. I'm just removing the radical, okay? So basically you have this 1 minus the cosine of theta over 2. Now be careful here because 9 is multiplying this whole thing, okay? If you end up distributing this to the numerator, make sure you use parentheses, okay? Very important. What I'm going to do first is rearrange things. So I'm going to put this as cosine squared theta, okay? Then minus 4 times cosine of theta, and then basically plus 4, okay? So I've got all my signs right. I want to make sure on that. And then this equals, let's do 9 times 1 minus cosine of theta like this, okay? Because the 9 is multiplying the 1 and also the negative cosine of theta. Then this is over 2, okay? So now what I'm going to do is I'm going to multiply both sides by 2 so that I can clear this denominator, okay? So basically this comes here and cancels here. And here I'm just going to put a 2, okay, being multiplied by everything there. So you'd have 2 times the cosine squared theta. And then I would basically have minus 8 times the cosine of theta. And then plus I would have 8. And this equals, the 2's canceled. So just let's go ahead and distribute this. So 9 minus 9 times the cosine of theta. Okay. So far, so good. Let's scroll down just a little bit more. Okay. So what I want to do here is basically subtract 9 away from each side of the equation and also add 9 times the cosine of theta to each side of the equation, okay? So basically what this is going to do is give me a 0 on the right, okay? You can see where I'm going with this. I'm going to end up factoring and using the zero product property. So on the left, I have my 2 times the cosine squared theta. And then basically I have negative 8 cosine of theta plus 9 cosine of theta. So this is going to be plus cosine of theta, or you could say plus 1 times the cosine of theta, whatever you want to do there. And then basically 8 minus 9 is negative 1, and this equals 0, okay? So the idea here is that, of course, if you wanted to, you could use the quadratic formula, but we have something that is factorable. So let me go ahead and cut this away, put that in there. So I'm just going to factor the left side here. Again, if you have trouble factoring this, I see a lot of students having trouble, write it as 2u squared plus u minus 1 equals 0. You can factor that no problem, right? You think about this as 2u and u, and then the last guy here is a negative 1, right? So that tells me I need mixed signs here. This guy is going to be positive. So what I want to do is put a plus 1 here and a minus 1 here, right? Because the outer would be 2u and the inner would be minus u, so that would give me the correct plus u there, okay? Now, once you've factored it like this, you can just put your cosine of theta in for u, okay? So let's come back in here, replace this with cosine of theta, and your roadblock is gone. Okay, so 2 times cosine of theta there. Okay, so a little trick for you. Now, I'm going to set each one of these equal to 0 and solve. Let me just get rid of this. We don't need this anymore. So I'll say 2 times the cosine of theta minus 1 equals 0. Or I'll say the cosine of theta plus 1 equals 0. Let me scroll down and get a little room going here. So basically, I'm going to add 1 to both sides. And this is going to give me 2 times the cosine of theta is equal to 1. Okay, I'm going to now divide both sides by 2. And I get cosine of theta is equal to 1/2, okay? Over here, let me go ahead and put or, and I'll put or. And then over here, I'm just going to say minus 1 minus 1. So the cosine of theta is equal to negative 1. And I guess I don't really need another one there, so let's put this over here. Well, I guess I could write it down here. So cosine of theta equals negative 1. Okay, so you see what we're doing here. We basically have to solve this guy and then this guy. So where's cosine going to be equal to 1/2? Remember, cosine is positive in quadrants 1 and 4. And we know that cosine of 60 degrees, okay, is 1/2. So basically, you would want a 60-degree reference angle in quadrant 4. So that would be 300 degrees, right? So you'd want 60 degrees and then 300 degrees. Again, if you're still looking at your unit circle, it's no big deal, right? This is 1/2 here. So you see it's 60 degrees or pi over 3 in terms of radians. And then over here, you'd be in quadrant 4, so you have 1/2 here, 300 degrees or 5 pi over 3 in terms of radians, okay? So again, if you need to use the unit circle, keep doing it. You will memorize it eventually. Now, while we're down here, I might as well note that basically pi, okay, cosine of pi is going to give you negative 1. So let's go back up, and let me erase the degrees, and let me say that theta here would be equal to your pi over 3, and then it would be 5 pi over 3, and then it would also be pi, right? So this covers these solutions from these guys. Now, in order to make the video a little bit shorter, a little bit more concise, I'm not going to check these solutions. When you square both sides of an equation, we know from basic algebra that there's a possibility of extraneous solutions, right? Solutions that won't work in the original equation. I have already checked this. I know that these guys are going to work. I can say that the solution set here is pi over 3, okay? And then I'll say pi, and then I'll say 5 pi over 3 like this, okay? So these solutions do work in the original equation. In the next example, we'll see where it doesn't, okay? So let's go to that now. All right, let's look at another example here. So we have the square root of 3 times the cosine of theta over 2 is equal to 1 plus the cosine of theta, okay? Again, same interval from 0 to 2 pi, 0 is included. Again, if you see something like this, you have cosine of this and cosine of this, well, you can go ahead and use your identity. So we come back here. Now, cosine of, in this case, would be theta, theta over 2, is plus or minus the square root of 1 plus the cosine of theta over 2. So let's just make a little substitution here. I'll say the square root of 3, okay, and I'll put the plus or minus out in front of here, then times my square root of 1, in this case, it's plus the cosine of theta. Remember, if it's sine, then it's minus. If it's cosine, it's plus. And then this is over 2. And this equals your 1 plus your cosine of theta, okay? So again, all I need to do here is just square both sides. So let's square this side, and let's square this side, okay? And over here, the plus and minus, forget about it, it's gone. Square root of 3 squared is 3. This guy, if I square it, I'm basically going to end up with the radicand. So this is 1 plus the cosine of theta over 2. And to speed this up, let me just wrap this in parentheses and put this like this. And let's put equals over here. I'm going to flip these. I'm just going to put the cosine of theta plus 1, so it makes it easier. So cosine of theta plus 1 like this. So this would be the cosine squared theta, first guy squared, plus 2 times the first guy times the second guy. So it's basically just 2 times cosine of theta, and then plus the last guy squared, so that would be 1. Okay? So over here now, all we need to do is basically multiply everything by 2, right? So this would cancel. Let me show this visibly. And let's go over here and do this. So now I have 3 times 1, which is 3, plus 3 times the cosine of theta. And this equals 2 times the cosine squared theta, plus you'd have 4 cosine, and I messed that up. So cosine of theta, and then plus 2 times 1 is 2. So from here, because I have a squared term, I want to think about either factoring or using the quadratic formula. This one's going to be factorable, so we'll be safe there. Basically, let's move everything to the left because that's where I like it. So let's subtract 2. So basically, this is going to be 1. Let's go ahead and subtract 4 times the cosine of theta. So minus 4 times the cosine of theta. So this is going to be negative cosine of theta. And then let's subtract 2 times cosine squared theta. So I'm running out of room over here. So let's just kind of put this over here. So minus 2 times cosine squared of theta. I know it's kind of getting a little messy, but let's just write it neatly now. So we'll put this out in front. We'll put negative 2 times cosine squared theta. And then we'll put minus cosine of theta. Then we'll put plus 1. And of course, everything's gone from over here, so this equals 0. If you want, for factoring, a lot of people do not like to factor with a leading coefficient that's negative. You can multiply everything by negative 1. So this becomes positive. This becomes positive. This becomes negative. And it has no effect on 0. Okay? So basically, if I want to factor this, again, you can use that trick with u if you want. I don't really need to do it. So I'm just going to put 2 times cosine of theta and cosine of theta, okay, because this times this would give me this. Now, the final guy is negative 1. So that can only come from positive 1 times negative 1. We know that this guy right here is positive, so that means I want to put plus 1 here and minus 1 here, right? Because the outer would be 2 times cosine of theta, the inner would be minus cosine of theta, so that would combine and give you this, okay? So let's go ahead and copy this and paste this in another sheet. And again, I'm just going to use my zero product property. I'm going to say 2 times the cosine of theta minus 1 equals 0. Or the cosine of theta plus 1 equals 0. So I'm going to add 1 to both sides over here. And I'll have 2 times the cosine of theta is equal to 1. Divide both sides by 2. And again, we get this cosine of theta is equal to a half. So we already know that that's going to occur basically at 60 degrees, right? Or a reference angle of 60 degrees in quadrant 4, which is 300 degrees. Let me just drag this up here. We'll say that theta here is 5 pi over 3, or actually let's do this first. So we'll do pi over 3, or then 5 pi over 3. So again, this guy right here is your 60 degrees. This guy right here is going to be your 300 degrees. Okay, so then or, okay, and I'll just put a comma here. For this one, it's really simple. I just go minus 1 here, minus 1 here. So we have the cosine of theta is equal to negative 1. We already know this is going to be pi. Okay, so we've seen this before. So this is exactly the same solution that we got in the last section or the last example, but basically now you're going to see that one of them is not going to work. So let's actually erase all of this. We know it's a pain to check solutions, but it's absolutely necessary in this case. So my original equation is the square root of 3 multiplied by the cosine of theta over 2, okay? And then basically you have is equal to 1 plus the cosine of theta. So what do I have here to start? Let's go square root of 3 times, you would have the cosine of, basically you would have pi over 3 divided by 2. So it's like multiplying by a half. So it's the cosine of pi over 6. And the cosine of pi over 6, remember pi over 6 is 30 degrees, so that's going to be square root of 3 over 2. So let me just write this over here for reference. So cosine of pi over 6 is square root of 3 over 2, okay? So let me erase this, and I'm going to put square root of 3 over 2. This equals 1 plus the cosine of theta. In this case, we're working with our pi over 3. Let me write this in. So the cosine of pi over 3. And we already know that this is 60 degrees here. So this would be 1/2, okay? So what is 1 plus a half? Most of you know this would be 2 over 2 here. So 2 over 2 plus 1 over 2 would be 3 over 2, or basically 3/2. Now, if I do square root of 3 times square root of 3, that is 3, okay? So this does give me 3/2. So the first solution is valid. So this one you can put a big fat check, okay? The next one you're going to see a problem with. So let's go ahead and erase this and try again. So we have the square root of 3 times, I'm putting 5 pi over 3 in here. Remember, if I do 5 pi over 3, let me erase this. We're not going to need this anymore. So if I do 5 pi over 3, and then divided by 2, it's like having cosine of 5 pi over 6. Now 5 pi over 6 is 150 degrees, so that has a 30-degree reference angle, and it's in quadrant 2, so it would be the negative of the square root of 3 over 2, okay? So this is the negative of the square root of 3 over 2, okay? Over here I have 1 plus the cosine of 5 pi over 3, and we already know this is going to be a half, right? So we know this is a half, this ends up being 3 halves. And you can see this is not going to work out because of the sign, right? Square root of 3 times square root of 3 is still 3, but now it's going to be basically negative of 3 halves equals 3 halves. So this is false, right? This does not work. So this is what I mean by checking the solutions. If you don't check them, there's a chance, it's not going to happen every time, but there's a chance that you report a wrong answer, okay? Something that doesn't work in the original equation. Now this last one's going to work. If I put a pi over 2 in here, remember pi over 2 is 90 degrees, and cosine of 90 degrees is 0, right? So if I did square root of 3 times 0, well, that's 0, right? So you can basically say this is 0 over here. And then on this part, I have 1 plus the cosine of pi, and the cosine of pi, or the cosine of 180 degrees, is going to be negative 1. So what is 1 plus negative 1? That's going to be 0. So you get 0 equals 0, so this one checks out as well, okay? So let's go ahead and erase this, and we can finally write our solution set. I know this is super tedious, but it's just something you have to do. So we end up with pi over 3, okay? And then we end up with pi. These are the only two solutions in the interval we're given, from 0 degrees, or from actually 0 in terms of radians, out to 2 pi in terms of radians. So 0 is included, 2 pi is not. In this lesson, we want to talk about solving trigonometric equations with multiple angles. All right, let's take a look at the first problem. So here we have the cosine of 2 beta is equal to negative 10 cosine squared beta plus 8. Now we just want to solve this from 0 to 2 pi, where 0 is included and 2 pi is excluded. Now when you look at this, if I'm trying to get cosine of beta equals some number, here you have cosine of 2 beta, here you have cosine squared beta. So this one right here is going to be the immediate problem for us, because you want to write this in terms of the cosine of beta, again, equals some number in the end. So what you would want to do is use a little identity to plug in for this guy. And coming down here, this is the one I'm going to work with. If you have cosine of 2 theta or 2 beta, whatever you're working with, you have 3 different formulas you can choose from. I'm going to work with this one. So what I'm going to do is say the cosine of 2 beta is equal to 2 cosine squared beta minus 1. So I'm just matching this formula here. I'm just taking the beta in the place of theta. And basically now you have cosine of 2 beta and cosine of 2 beta. So those match. And what you can do is take this guy right here, and you could just plug it in for this guy right here. And that's going to give me cosine squared beta over here and cosine squared beta over here. So that's what I want. So let's write this as 2 cosine squared beta minus 1, again, just taking this and plugging it in for this. So that's how I get this left side now. So this equals, on the right, nothing's going to change. So this is just negative 10 cosine squared beta and then plus 8. Okay, at this point, I want to get cosine of beta equals some number. If you have a squared guy involved, then you should be thinking about factoring, or in some cases, the quadratic formula. But for this particular problem, you could actually solve it using the square root property, and it's going to be a lot faster. You could solve this with factoring if you want to, but it's going to take a little bit more time. So what I'm going to do is isolate cosine squared beta on one side and then have a number on the other side so I can use the square root property. So I'm going to add 10 cosine squared beta to both sides of the equation, just like that. And so right here, this is going to cancel. And then the other thing I'm going to do is add 1 to both sides of the equation. So this is going to cancel. So on the left, you have 2 cosine squared beta, then plus 10 cosine squared beta. That is 12 cosine squared beta. And this equals 8 plus 1 is going to be 9. Now what you would want to do, since 12 is multiplying the cosine squared beta there, you would divide both sides of the equation by 12. So you want cosine squared beta by itself to use the square root property. Okay, so this right here is going to cancel, and you get cosine squared beta is equal to, for 9 over 12, again, each is divisible by 3, so 9 divided by 3 is going to be 3, and 12 divided by 3 is going to be 4. So this is cosine squared beta is equal to 3/4, and now we can use our square root property. Again, if we have something like, let's say, x squared equals 3/4, then by the square root property, we can say x is equal to plus or minus the square root of 3/4. So that's the square root of 3 over the square root of 4, which is 2. So x would be equal to plus or minus the square root of 3 over 2. Well, here it's the same thing. I'm just going to get that cosine of beta is equal to plus or minus the square root of 3/4. And again, this becomes the square root here of 3 over the square root of 4. And the square root of 3 really can't do anything with that, but the square root of 4 is going to be 2. So the cosine of beta is equal to plus or minus the square root of 3 over 2. Okay, let's come to the unit circle, and let's actually write this as the cosine of beta is equal to the square root of 3 over 2, and then I'm going to write or the cosine of beta is equal to the negative of the square root of 3 over 2. So for beta here, we're going to look in quadrants 1 and 4, where cosine is positive, and I'm looking for an x-coordinate of square root of 3 over 2. So right here at pi over 6, and then coming down here, it's going to be at 11 pi over 6. So notice it's pi over 6 here, and then a pi over 6 reference angle here at 11 pi over 6. Then if I'm looking for cosine of beta to be equal to negative square root of 3 over 2, well, I'm looking in quadrants 2 and 3, where cosine is negative. So you can just think about a pi over 6 reference angle, or again, you could just look for that x-coordinate of negative square root of 3 over 2. So that's going to be right here at 5 pi over 6, again, pi over 6 reference angle, and then right here at 7 pi over 6, again, pi over 6 reference angle. So because we're working in the interval where beta is greater than or equal to 0 and less than 2 pi, we can just list these 4 solutions and be done with it. So we're going to say that beta is equal to, we have pi over 6, we have 5 pi over 6, and then we have 7 pi over 6, and then lastly, we have 11 pi over 6. All right, let's take a look at the next problem. So here we have 4 sine of beta cosine of beta equals the square root of 3. We want to solve this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So the first thing is, when you look at this equation, it might not be immediately obvious what you can do, but if we look at our identities, again, you have something like this double angle identity, the sine of 2 theta equals 2 sine of theta cosine of theta, which you can use to solve this equation. So I'm going to write this as the sine of 2 beta is equal to 2 sine of beta cosine of beta. Come back up here and paste this in. Now, this might not be immediately obvious, but we're going to take this right here and match it with this right here. Now, right now you have this 4 right here, and you have this 2 right here. So you've got to rewrite this to where it's going to match. So this is just straight multiplication. So for 4, I could really write that as 2 times 2. So I could say that this is 2 times, and then it would be 2 sine of beta cosine of beta, and this equals the square root of 3. So this 2 times 2 sine of beta cosine of beta gets me back to 4 sine of beta cosine of beta. So I haven't done anything illegal. If you look at this guy right here, now it matches this guy right here perfectly. 2 sine of beta cosine of beta, 2 sine of beta cosine of beta. So that means I can legally take this right here and I can plug it in for this right here. So what that's going to do for me is I'm going to have 2 sine of 2 beta equals the square root of 3. So I'll be able to get it to sine of 2 beta equals some number, and I'll be able to get a solution. So let's go down and make a little substitution here. So I'm going to have my 2, don't forget about that. And then what is it multiplying? Again, for this, I'm plugging in this. So I'm going to have my sine of 2 beta, and this equals my square root of 3. All right, so just like I said, we want to get sine of 2 beta equals some number. Right now you have 2 that's multiplying the sine of 2 beta. So let's divide both sides of the equation by 2. So this is going to cancel, and we're going to get the sine of 2 beta is equal to the square root of 3 over 2. All right, there are quite a few ways you could solve this. What I'm going to do is stick to the method that the book uses because we're solving over a specific interval. We're not giving the general solution. So I'm going to start with the interval we were given. So we have beta is greater than or equal to 0 and less than 2 pi. Well, right now I have 2 beta. So I'm going to multiply each part of this inequality here by 2. So 0 times 2 is still 0, and this is less than or equal to. Beta times 2 is 2 beta. So now this matches this, and then this is less than 2 pi times 2 is 4 pi. So right now, I'm going to work in this interval because, again, I have the sine of 2 beta, not the sine of beta. So that's why I'm adjusting this interval. So let me move this up here, and we're going to think about where are the sine values square root of 3 over 2 in this interval right here. So let's start with the standard interval. So just going from 0 to 2 pi, 0 included, 2 pi excluded, and that's going to give you a pi over 3 solution. So there's your square root of 3 over 2 for the y value, and then here's your square root of 3 over 2 for the y value as well. So that's at 2 pi over 3. But again, to get all of the solutions in this interval, what you have to do is take those solutions and you have to add 2 pi to them in order to get all the solutions in this interval. So I'm going to take and list pi over 3, and then let me list 2 pi over 3. And then what I would have to do is, again, take pi over 3, so pi over 3, and I've got to swing around by another 2 pi. So let me go plus 2 pi, so that's 6 pi over 3 if I get a common denominator. Let me make that 3 a little bit better. So that's 7 pi over 3. So let's put that up there. So that's 7 pi over 3. So again, starting here, just swinging around by another 2 pi. You've got to do the same thing here. So you're going to swing around by another 2 pi. So let's put this as 2 pi over 3 plus, again, 6 pi over 3. So 6 pi over 3 is, again, 2 pi written with a common denominator. So this would be 8 pi over 3. So 8 pi over 3. So that's basically all you have to do for this part. The only thing is you have not solved for beta. You've solved for 2 beta. So in other words, you could say that 2 beta is equal to this right here. Let me just drag this down. And I don't know if that's going to fit. And let me just grab this real quick and paste this in and go to another page. So basically, if you want to solve for beta, you would divide everything by 2, or you could multiply everything by a half. So in other words, you could say that beta is equal to, you'd have pi over 3 times 1/2. So that would be pi over 6. So pi over 6. And then you'd have 2 pi over 3 times 1/2. So the 2's would cancel there. So that would be pi over 3. So pi over 3. And then you'd have 7 pi over 3 times 1/2. That would give you 7 pi over 6. And then lastly, you'd have 8 pi over 3 times 1/2. So here, 8 divided by 2 would give you 4. So this would end up being 4 pi. So 4 pi over 3. So these are your solutions in terms of beta. So if you plug those back into the original equation, they will work, and they are in our interval where beta is greater than or equal to 0 and less than 2 pi. So beta is pi over 6, pi over 3, 7 pi over 6, and then 4 pi over 3. All right, let's take a look at another problem. So we have negative 9/2 is equal to negative 4 plus the cosine of beta plus 7 pi over 4. We're solving this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So I'm going to get cosine of beta plus 7 pi over 4 by itself. So that'll be on one side. There'll be a single number on the other side. So that's the first goal. So let me write this as negative 4 plus cosine of beta plus 7 pi over 4. And then this would be equal to, you have this negative 9/2. Now, if I want cosine of beta plus 7 pi over 4 on one side by itself, I've got to get rid of this negative 4 here that I'm adding to this. So I'm going to just add 4 to both sides of the equation. This will cancel. And on the left, I have what I want. So this is the cosine of this beta plus 7 pi over 4. And this equals, over here I would get a common denominator. So let's write 4 as 8 over 2. I'm just going to multiply by 2 over 2 to do that. So again, this would be 8 over 2. So 8 over 2. And negative 9 plus 8, that's negative 1. So this would be over the common denominator of 2. So this is equal to negative 1/2. Now this is the part where people tend to get confused. Essentially what you're going to do is adjust your interval. You don't have beta. So if you were solving cosine of beta equals negative 1/2, well then I could go through and I could say, well, where's the x coordinate negative 1/2? We're going to have right here at 2 pi over 3. And then you come over here, and that's going to be at 4 pi over 3. We don't have that, though. We have this beta plus 7 pi over 4. We don't have beta. Well, I can adjust that interval. We had beta is greater than or equal to 0 and less than 2 pi. Well, instead of beta, I have beta plus 7 pi over 4. Okay, well, I'm just going to add 7 pi over 4 to each part. So 0 plus 7 pi over 4 is 7 pi over 4. This is less than or equal to beta plus 7 pi over 4 is beta plus 7 pi over 4. So this matches this, and this is less than 2 pi plus 7 pi over 4. So if we do 7 pi over 4 plus, let's go 8 pi over 4, just writing 2 pi with a common denominator, this would be 15 pi. So 15 pi over 4. So 15 pi over 4. So if we had cosine of beta equals negative 1/2, again, I would have this 2 pi over 3 and this 4 pi over 3. But in this case, we have the cosine of beta plus 7 pi over 4. So when I adjust this interval to this one right here, let me get rid of this one right here so this is crystal clear. What I'm going to do is look for where the cosine value is negative 1/2 in this interval. So you would start at 7 pi over 4. So in other words, you've already swung around by 7 pi over 4, and then you want to swing around by another 2 pi to end up at 15 pi over 4, even though that's not included. So you're going to catch this guy right here and this guy right here again, but it's not going to be 2 pi over 3 or 4 pi over 3. It's going to be you adding 2 pi to those angles. So what you would do is you would say that beta plus 7 pi over 4 would be equal to, you're going to take this 2 pi over 3, so 2 pi over 3, but now you've got to add 2 pi to that. So that's going to be me adding 6 pi over 3. So that would give me 8 pi over 3. So you can get rid of these middle steps here and just say this is equal to 8 pi over 3. We'll solve this for beta in a moment. Let's just do the other one. So then again, you have this beta plus 7 pi over 4 is equal to, again, you're going to take this 4 pi over 3. So this 4 pi over 3, and then you're going to add 2 pi. So you're going to say this is plus 6 pi over 3. So this gives you 10 pi over 3. Let me move this down here so this is more clear. Now I know the first time you do this, this is super confusing, but just think about the fact that, again, you started here at 7 pi over 4. That's where the interval is beginning. So if I'm starting here, by the time I swing around, this is not 2 pi over 3. This is 2 pi over 3 plus 2 pi. So that gives me that 8 pi over 3. And then as I continue, this is not 4 pi over 3. This is going to be 4 pi over 3 plus 2 pi. So that's that 10 pi over 3. So you've got to adjust things because we're not solving cosine of beta equals negative 1/2. We are solving cosine of beta plus 7 pi over 4 equals negative 1/2. So everything got adjusted. So let's go ahead and grab this. And I'm just going to come down here and we can solve these pretty easily. So let's go OR there. I'm going to subtract 7 pi over 4 away from each side of the equation over here. So this is going to cancel. You're going to have beta is equal to 8 pi over 3 and then minus 7 pi over 4. You need a common denominator, so let's multiply by 4 over 4. Let's multiply this by 3 over 3. So this would be 32 pi over 12. So 32 pi over 12, 21 pi. So 21 pi over 12. So this would give me 11 pi, so 11 pi over 12. So that's one solution. Let me get rid of this and just write this as beta is equal to 11 pi over 12. And let me solve this one now. So I'm going to subtract 7 pi over 4 away from each side of the equation. So that cancels. You get beta is equal to, let's go 10 pi over 3. I'm going to just multiply this by 4 over 4 now to get a common denominator, and then minus 7 pi over 4 times 3 over 3. So we will say that beta is equal to 10 pi times 4 is going to be 40 pi, and this is over 12, and then minus 7 pi times 3 is 21 pi. So 21 pi, and this is over 4 times 3 is 12. So 40 pi minus 21 pi is 19 pi. So this is 19 pi over 12. Let me just put a comma here and put 19 pi over 12. So those are your solutions in that given interval, again, where beta is greater than or equal to 0 and less than 2 pi. Okay, let's take a look at another problem. So here we have the cosine of 6x is equal to negative sine of 4x plus the cosine of 2x. So here we're going to solve over this interval from 0 to pi, where 0 is included and pi is excluded. When you solve a problem like this that involves these sum to product identities, in most cases, you're not going to solve that over an interval because there's just too many solutions. You will give the general solution. Let me start this problem off as saying we have the cosine of 6x. I'm going to add the sine of 4x to both sides, and I'm going to subtract the cosine of 2x away from each side. So let me subtract away the cosine of 2x first. So I have this. And then I'm going to add sine of 4x. And then we're going to say this equals 0. Okay, let's grab this real quick. And let's come down here. So I have our little identities set up for us. So these are the, again, sum to product identities. So we have this cosine of A minus cosine of B. Here you have cosine of 6x. So 6x is your A minus cosine of 2x. So 2x is your B. Let me actually slide this down and I'll write this out first and then we'll plug in. So if you had the cosine of 6x minus the cosine of 2x, so I'm just going to do this part right here. This is equal to -2, and then sine of, you have a plus b over 2. So this plus this. So 6x plus 2x over 2. And then you have your sine of a minus b over 2. So 6x minus 2x. So 6x minus 2x. Again, this is over 2. 6x plus 2x is 8x. So this right here would be 8x over 2. So this 8 would cancel with this 2 and give me a 4. So this would be 4x right here. So let's write that like that. I'm just going to wrap this for clarity. And then here, 6x minus 2x is 4x. And so this would be 4x over 2, which is 2x. So let's write the sine of 2x. Now, since this right here matches this right here, we can take this guy right here and plug it in for this right here. Now, why are we doing that? Notice you'd have a sine, and then you have a sine. And more specifically, you have this 4x here and this 4x here. So we're going to be able to actually solve this with factoring. So let's come down a little bit and let's plug in. So this goes in here. So -2, and then sine of, you have your 4x, and then sine of, you have your 2x, and then plus your sine of 4x, and this equals 0. So you have your sine of 4x and your sine of 4x. So we are going to factor that out. So let's factor that out. So out in front of some parentheses, you would have the sine of 4x, and then inside, you would have -2 sine of 2x. So -2 sine of 2x, and then plus, if this gets pulled out, you're going to have a 1, and then this equals 0. Now at this point, you can use your zero products property. So you can say that the sine of 4x is equal to 0, or we're going to do this one. So -2 sine of 2x plus 1 equals 0. In this particular case, you have sine of something. It doesn't matter what it is. In this case, it's 4x equals 0 or some number. This is okay. For this, when you want to clean it up, you would want sine of 2x equals some number. So let's go ahead and subtract 1 away from each side. This cancels. So actually, let me just erase it so we can save some space here. And then I would divide both sides by -2. So this would cancel. So you're going to get the sine of 2x is equal to 1/2. So positive 1/2. Now, here's where you need to make a decision. Again, in most cases, you're going to solve for the general solution. And when I solve for the general solution, I like to use a substitution technique. So you can do it this way if you want. If you're solving over an interval, you can do it the normal way that we've been doing it by adjusting our interval. So instead of sine of 4x equals 0, for this particular one, I'm going to let u be equal to 4x. Now this has nothing to do with this. So actually, let me cut this away and put this on another page so nobody's lost, because people will get confused. So now I can solve this, let me get rid of this or, by saying that I have the sine of u is equal to 0. So if I look at the sine of u equals 0, using my unit circle, let me write this in. So the sine of u equals 0. So if you look at this guy is 0, so that's at 0, and then this guy is 0, that's at pi. So you could write that u, in terms of the general solution, is equal to 0 plus 2 pi n, and then you could say pi plus 2 pi n, where n is any integer, because things are going to repeat every 2 pi in terms of u. Now, what you could actually do is write this as 2 pi n, and then pi plus 2 pi n, but you would notice that actually you can combine those solutions and make it a little bit more concise, because things are happening every pi. So in other words, I could just write this as pi n. So I could write this as pi n, because if I plugged in a 0 for n, I'd have 0. If I plugged in a 1, I'd have pi. If I plugged in a 2, I'd have 2 pi. At 3, I'd have 3 pi, so on and so forth. So this is the general solution in terms of u. So let's come back up, and let's say that u is equal to pi n. Now, we let u be equal to 4x. So all I have to do is plug in a 4x for u. So 4x is equal to pi n, and then just solve for x. How do I do that? I divide both sides by 4. So this would cancel, and you're going to get that x is equal to pi over 4 times n. So let me get rid of this and bring this over here. So x is equal to pi over 4 times n. Now, we will get our solution in the interval in a moment. Let me get rid of this, and let me come down here and solve this. So I'm going to use u again, but it's only in terms of this. It has nothing to do with what we did before. And actually, so nobody gets lost, let me just pick something else. Let me let w, so nobody is confused, be equal to 2x. So now I want to solve the sine of w is equal to 1/2. Come back to the unit circle, and let's think about this. Again, sine of w equals 1/2. Well, we know how to solve that. We know that solutions are going to repeat every 2 pi. So where's the y-coordinate 1/2? So right here at pi over 6, and then that's going to be right here at 5 pi over 6. So we can say that w is equal to pi over 6 plus, again, these solutions repeat every 2 pi. Again, this is in terms of w, so we're going to say 2 pi n, and then we're going to have 5 pi over 6 plus 2 pi n. Again, things are happening every 2 pi in terms of w. Okay, so in terms of w. So let's grab this. All right, so let's come back here. Let's get rid of this. And now w is 2x. So all you have to do is go back and say, okay, well, 2x is equal to, we have pi over 6, and then plus you have 2 pi n. The other one is 2x is equal to 5 pi over 6 plus 2 pi n. Let me get rid of this. And actually, I probably should slide these over a little bit because I have to do some multiplication here. Let me make that border a little bit better. And let me slide this down just a little bit and slide this up just a little bit. Now, we have 2x, not x. So if you want x by itself, you can divide everything by 2, but because we have a fraction involved, it's better to multiply by 1/2. It's just a little bit easier to do it that way. Let me get rid of this border here. So multiply by 1/2, and then multiply by 1/2. So we know that this would cancel and just give me x is equal to pi over 6 times 1/2 is pi over 12. And then plus 1/2 times 2 pi n, the 2's would cancel. You just have pi n. So get rid of this. So that's one guy there. Let me move this over. And then this guy, I'm going to do the same thing. So let me move this up. I'm going to multiply this by 1/2, multiply this by 1/2, and multiply this by 1/2. So we're going to see that the 2's are going to cancel. You're going to have x is equal to, if you have 5 pi over 6 times 1/2, well, we would have 5 pi over 12. And then plus, again, the 2's would cancel. So you're going to get pi n. So let me get rid of this. And actually, this color really doesn't show up very well. So let me change this and say that x is equal to pi over 12 plus pi n. And then we have 5 pi over 12 plus pi n. Okay, let me bring this back here. And now let's put our solution together. So right now I'm giving you the general solution, and then I'll give you the solution over an interval. So for the general solution, you're going to take this one. So we're going to say that we have pi over 4 times n. Then if we think about this one, we have pi over 12 plus pi n. And then this one is 5 pi over 12 plus pi n. That's our general solution. Now, if we want to go with the solution where x is greater than or equal to 0 and less than pi, well, again, you're going to start here and plug in a 0 for n. So that would give you, let's go x is equal to 0. And if I plugged in a 1, I'd have pi over 4. If I plugged in a 2, I'd have 2 pi over 4, which is pi over 2. If I plugged in a 3, I'd have 3 pi over 4. If I plugged in a 4, I'd have 4 pi over 4, which is pi, and that's not in this interval. So I'm going to stop there. And then these, you would have pi over 12 if you plugged in a 0 there. And then if you add pi, you're not going to be in this interval. So then this one, I would have 5 pi over 12. So 5 pi over 12. Again, if I add pi, I'm not going to be in this interval. So these are your solutions in this interval. So 0, pi over 4, pi over 2, 3 pi over 4, pi over 12, and then 5 pi over 12. Okay, so I want to think about this graphically with you. If you're struggling with finding the general solution, this can be extremely helpful, although it's extremely time-consuming to think about this with a graph. So we have y equals the cosine of 6x minus the cosine of 2x plus the sine of 4x. So this was my equation. It's just that instead of y, we had 0 over here. So if I plugged in a 0 for y, so in other words, if I had 0 is equal to the cosine of 6x minus the cosine of 2x plus the sine of 4x, all I'm doing is I'm saying, for which x values am I going to get a y value of 0? Well, where is y0 when I'm thinking about this on the coordinate plane? Well, that's on the x-axis, right? So that's where y is 0. So anywhere where I cross the x-axis or have an x-intercept, I'm going to have a solution for this equation. So thinking about this, where x is greater than or equal to 0 and less than pi, I get this graph right here. Now, in a moment, we're going to talk about the fact that the period for this guy is going to be pi. We discussed this in the last practice test. Maybe you didn't watch the video for that, but I'll explain where this is coming from in a moment. So that means that I can go from 0 to pi, and I'm going to include 0 and exclude pi, and any solutions I find will actually repeat in that next cycle. So I could just take that solution and add pi. But you're going to see that you can condense some of those solutions and make it a little bit simpler. And let's just start with what we have. So notice that you have this 0 here, so that matches this one. I'm going to skip this one over for a moment. So we have this pi over 4, so that's there. I'm going to skip this one, so this is pi over 2, so that's there. And then I'm going to go to this one, which is 3 pi over 4. Now, if you think about those solutions, you have 0, and then you have pi over 4, and then you have pi over 2, and then you have 3 pi over 4. Again, you could go through and say plus pi n, and then plus pi n, and then plus pi n, and then plus pi n. That is valid. But what's happening is, if you add pi to this, let me just show if I added pi, this would get me to pi. If I added pi to this, I would be adding 4 pi over 4, so this would get me to 5 pi over 4. If I added pi to this, that would get me plus 2 pi over 2, so that would be 3 pi over 2. And then if I added pi to this, I would add 4 pi over 4, so that would get me to 7 pi over 4. Well, if you go through here and you just look at these first guys here, so it would be a jump of pi over 4 each time. So 0 plus pi over 4 is pi over 4. Pi over 4 plus pi over 4 is pi over 2. Pi over 2 plus pi over 4 is 3 pi over 4. 3 pi over 4 plus pi over 4 is pi. Pi plus pi over 4 is 5 pi over 4. 5 pi over 4 plus pi over 4 is 3 pi over 2. 3 pi over 2 plus pi over 4 is 7 pi over 4, and so on and so forth. So that's why we got that pi over 4 times n with the general solution. So we have this pi over 4 times n. Then the other ones, you really can't do anything with them other than to say that you have pi over 12, so that's this one right here, and then just plus pi n. So it's just going to repeat in the next cycle. So this is pi over 12 plus pi n. Let me slide this down. And then the other one, we have 5 pi over 12, so that's this here. So again, that's just going to repeat in the next cycle. So 5 pi over 12 plus pi n. All right, let's come to the graph. Now, these solutions are extremely hard to read, so you probably need to follow me on Desmos or something like that in order to fully see everything. But I'm just going to first talk about the period for this guy. I'm going to let you visually see that and explain where it's coming from. So in the practice tests for the last lesson, we talked about the fact that if you had something like y equals the cosine of 6x minus the cosine of 2x plus the sine of 4x, if you wanted the period for this, then basically you would think about the least common multiple of the periods. So how do you get the least common multiple of the periods? So this right here, you'd think about it as, let's just say you had y equals the cosine of 6x. What's the period? Well, it's going to be 2 pi over 6, right? 2 pi over 6, which is pi over 3. So pi over 3. Again, that's coming from that formula. If you have y is equal to the cosine of bx, well, it's 2 pi, which is the standard period for cosine, divided by b. So here it's 2 pi divided by 6, so that gives me pi over 3. It's the same thing if you run into sine, right? So sine and cosine is the same thing. So let's do this one. So this is the cosine of 2x. So that's 2 pi over 2. So that gives me just pi. And then for this one, it's the sine of 4x. So that's 2 pi over 4. So that's pi over 2. So we have not discussed how to find the least common multiple of fractions. So in other words, let's say I said, what is the least common multiple of 1/3, 1, and 1/2? Well, some of you know that it's going to be 1, but others don't. Now, there's a formula you can use for it, but it's a little bit complicated, actually, if you ask me. I think it's a little bit faster to just list things. So if you had something like pi over 3, all you're doing is you're multiplying it by 1, then 2, then 3, then 4. You're generating some multiples. So times 1, it would just be pi over 3. And then times 2, it would be 2 pi over 3. And then times 3, it would be 3 pi over 3, which of course is just pi. And then we could just do one more. So times 4, it would be 4 pi over 3. Let me put a border. For this one, if it's pi, well, that's real easy. Multiply by 1, you get pi, then 2 pi, then 3 pi. Let's stop at 4 pi. Then for the other one, you have pi over 2. So let's go times 1, it's pi over 2. Times 2, it's 2 pi over 2, which of course is going to just be pi. And then times 3, it's 3 pi over 2. Times 4, it's going to be 2 pi. And you could stop there. If you look at the least common multiple here, well, looking through, what do I have that's common to everything? You have pi, you have pi, and you have pi. So in other words, if you had 1/3, if you had 1, and you had 1/2, the LCM would be 1. But in this case, we have pi over 3, which can be thought of as 1/3 times pi. You have pi, which can be thought of as 1 pi. And then pi over 2, which you could think of as 1/2 times pi. So the least common multiple there is pi. So that tells me that the period for this graph here is going to be pi. Let me get rid of this. And let me actually trace this out so you can see it. If you want to follow me, type in x is equal to pi like this in Desmos. It's going to fix it for you and give you a pi like that. You're going to get a vertical line. And you can go x equals 2 pi, and then x equals 3 pi, so on and so forth. You're going to get these vertical lines, and it's going to really allow you to see the period of this guy. So I'm just going to trace from 0 to pi, and then we'll see that this is going to repeat from pi to 2 pi. So this right here, this is going to be one cycle for this graph. So this is one cycle. So from 0 to pi, and then again, if I went from pi to 2 pi, the same thing is going to repeat. So basically, I come up, come down, come back up, come down, come back up. So this is way up here. This is exactly matching what happened in the last cycle. So you can see that these two match and the period is going to be pi. So this tells me that things that happen from 0 to pi, 0 included, pi excluded, would happen again from pi to 2 pi, pi included, 2 pi excluded. So that's how we ended up on the last page, where I did this where you could see the solutions more clearly, and looks like I erased my 5 pi over 12. But as I was saying, it just shows you that solutions that happen in this cycle will repeat in the next cycle. So you could take your 0 plus pi n. You could take your pi over 12 plus pi n. You could take your pi over 4 plus pi n, so on and so forth. It's just that the 0, pi over 4, pi over 2, 3 pi over 4, those guys can be condensed into this form right here. So the pi over 4 times n, where n is any integer. And then for your pi over 12, well, you really can't do any better than just saying plus pi n. So you have your pi over 12, you add pi, that gets you to that 13 pi over 12. I know you can't see it, but it's right there. And then 5 pi over 12, again, if you add pi, you're going to be at that 17 pi over 12. Again, I know it's hard to see, but just follow it on Desmos if you want to look at it. So this is our general solution. Again, if you want to play around with the graph on Desmos, you can visually see this, and it'll help you to understand the concept of the general solution and how things are repeating. In this lesson, we want to talk about solving trigonometric equations with inverse trigonometric functions. All right, before we start looking at any equations, I want to review some concepts that are going to be important for today's lesson. So these are going to come from our lesson on inverse trigonometric functions. So I'm going to let f be a one-to-one function. What does it mean to have a one-to-one function? Again, if you go back to the definition of a function, you have a relation where for each x, there's one y. So you would look at the graph of the relation, and it needs to pass the vertical line test, so no vertical line would impact the graph in more than one location. And if it passes that, you have a function. So for each x, there's one y. Now, when you think about a one-to-one function, you start with a function, and you apply another rule where you say, now also, for each y, there's one x. So for that, you would check it with the horizontal line test. So no horizontal line would impact the graph of a one-to-one function in more than one location. If it does, that's not a one-to-one function. If it doesn't, then you're good to go and you have a one-to-one function. And if you have a one-to-one function, you can generate an inverse. So let's say f is your one-to-one function. The way you would notate your inverse, you would say it was f inverse like this. So again, this is not an exponent of -1. This is the inverse of my function f. The way you generate your inverse is you swap your x's and your y's. So the domain, or the set of allowable x values for f, becomes the range, or the set of allowable y values for f inverse. And then the range for f becomes the domain for f inverse. So in other words, if I look at a point on f, and let's say it's 3, 2, when I go to the inverse, these guys are going to be swapped. So the x will become the y, and the y will become the x. So this would be 2, 3. So your x value of 3 becomes your y value of 3, and that could be a lot better there. And then your y value of 2 will become your x value of 2 in the inverse. So following this thought process here, where the domain becomes the range and the range becomes the domain, what happens is when you look at your function and you compose it with its inverse, you're going to have this little cancellation that happens, or you can say these guys are going to undo each other. So f of f inverse of x is equal to x for every x in the domain of f inverse. And then f inverse of f of x is equal to x for every x in the domain of f. So this is something we're going to use today when we're solving our trigonometric equations. So as a practical example, just using what we have here, let's say you had f of f inverse of, let's say, 2. So using this right here, it should be equal to 2. So I can just give an answer of 2 right away. But if you wanted to prove this, you can go about it the long way. So you could say, what is f inverse of 2? Well, I come up here and I say, okay, here's an x value of 2. If I plug that in, I know that my output or my y value is going to be 3. So what I want to do is say that this is now f of 3. Okay, well, what is f of 3? Well, again, if I look at my x value of 3, the associated y value is going to be 2 now. So this is going to be 2. So again, f of f inverse of 2 is going to give me 2 at the end of the day. I can shortcut this and not go through this inside part. Now, when I look at the other one, in that case, we have f inverse of, let's say, f of 3. Well, again, I already know that this is going to give me 3. If I go about this the long way, again, if I start on the inside of this guy right here, well, what is f of 3? F of 3 is 2. So this would be f inverse of 2, and f inverse of 2 is going to be 3. So these guys are just undoing each other. Again, f of f inverse of x is equal to x as long as x is in the domain of f inverse, and then f inverse of f of x is equal to x, again, as long as x is in the domain of f. All right, let's continue reviewing our lesson on inverse trigonometric functions. So if we look at the graph of y equals the sine of x, we can see the domain is from negative infinity to positive infinity, and the range is from -1 to +1, with both being included. We can also see that it's not a one-to-one function. It would fail the horizontal line test. So if we want to find the inverse sine function, we can't start with just y equals the sine of x. We have to do something called imposing a domain restriction, and we're going to come up with this, what we call restricted sine function. So y equals the sine of x, where x is going to be greater than or equal to -π/2 and less than or equal to π/2. So I have this listed as the domain from -π/2 to π/2, with both being included. So when you restrict the domain, you end up with a one-to-one function with the same range. So the range is still the same from -1 to +1, with both being included. When you start with a restricted sine function and you swap the x's and the y's, you're going to generate your inverse sine function. So y equals the inverse sine of x, or you could say y equals the arc sine of x. And now the domain, which is from -1 to +1, both being included, is coming from the range of your restricted sine function. And then the range from -π/2 to π/2, again, both being included, is coming from your domain of the restricted sine function. Now, the reason it's important to know all that, when you start using the cancellation properties with sine, you need to understand when you're composing sine with its inverse, when are you going to be able to cancel things? So in other words, we like to cancel this with this and say, okay, well, the result of this is just going to be equal to x. But this is only true if x is in the domain of the inverse sine function. And the domain of the inverse sine function is from -1 to +1, with both being included. So the sine of the inverse sine of x is equal to x for x being greater than or equal to -1 and less than or equal to +1. If you pull out your calculator and you try to do sine of the inverse sine of 2, that is not going to give you 2 as a result. It's going to give you an error because 2 is not in the domain of the inverse sine function. All right, the next one is a little bit more challenging to understand. You can explain it with 2 different approaches. So if you have something like the inverse sine of the sine of x is equal to x, this is only valid for x being greater than or equal to -π/2 and less than or equal to π/2. So this is actually pretty important to understand. The first way to think about it is, let's say you look at the sine of x, that is not the restricted sine function. So we know that for this guy, the domain is all real numbers, and plugging something in from -infinity to +infinity is going to give you a result that's going to be from -1 to +1. So I'm just going to mark that out and say that what's going to be plugged in for the inverse sine function is going to be from -1 to +1. Well, you know that that's the domain for the inverse sine function. And I know that the range is going to be from -π/2 to π/2. So basically, I'm always going to get something out of this guy right here that's from -π/2 to π/2. But what's going to happen is if you don't plug in something for x in this interval right here, you can't just cancel. You'd have to evaluate the sine of x first and then take the inverse sine of that. If you think about it from the other approach, you could say that these guys are only going to undo each other if you're working with the domain from the restricted sine function, which is where x is greater than or equal to -π/2 and less than or equal to π/2. If you're within that domain, well, then the inverse sine of the sine of x is going to give you x. These guys are going to undo each other. Okay, using a similar thought process, again, when we start with y equals the cosine of x, it's not a one-to-one function, so we restrict the domain to where x is greater than or equal to 0 and less than or equal to pi, you're going to have the same range. So from -1 to +1, both being included. So again, if you start with that restricted cosine function and you swap the x's and the y's, you're going to get your inverse cosine function. So y equals inverse cosine of x, or y equals arc cosine of x, if you want to say it that way. Your domain is from -1 to +1, both being included, coming from the range of the restricted cosine function. And then the range is from 0 to pi, both being included. That's coming from the domain of the restricted cosine function. So here's something like the cosine of the inverse cosine of x is equal to x, for x being greater than or equal to -1 and less than or equal to +1. Again, you've got to be within the domain of the inverse cosine function for this to work. And then for this one, the inverse cosine of the cosine of x is going to be equal to x, for x being greater than or equal to 0 and less than or equal to pi. So again, you've got to be within the domain of the restricted cosine function for this to work. Again, the other way to think about this, you could say that the cosine of x, the domain for that is all real numbers. So I can plug in whatever I want, but the issue is, if it's not in this interval here, I've got to evaluate that first before I take the inverse cosine of it, because the inverse cosine is only going to give me something from 0 to pi, with both guys being included. So these guys will undo each other as long as x is in the domain of the restricted cosine function. So again, being greater than or equal to 0 and less than or equal to pi. And for the last one, we look at the tangent of x. So y equals the tangent of x. Again, not a one-to-one function. You restrict the domain to where x is strictly greater than -pi/2 and strictly less than pi/2. So -pi/2 and pi/2 are not included. And then when you look at the range, it's going to be all real numbers. So when you swap the x's and the y's, you get your inverse tangent function. So y equals the inverse tangent of x, or y equals the arc tangent of x. So the domain is all real numbers, again, coming from the range of the restricted tangent function. And then the range is going to be from -pi/2 to pi/2. Again, these guys are excluded here. Remember that the tangent of pi/2 or the tangent of -pi/2, those are undefined because the cosine of pi/2 is 0, and you'd have division by 0, which is undefined. So when we think about the range here, this is coming from the domain of the restricted tangent function. All right, so this first one's really easy to understand. So the tangent of the inverse tangent of x is equal to x for any x that is a real number. So that's what this means. This means x is an element of the set of real numbers. And basically, if you think about the domain of the inverse tangent function, again, it's all real numbers. So that's why we can plug in whatever we want here, and these guys will undo each other. When we think about this one, again, this is the one that's more tricky to understand. So the inverse tangent of the tangent of x, this is equal to x for x being greater than -pi/2 and less than pi/2. So this x is going to be in the domain of the restricted tangent function if you want these guys to undo each other. All right, let's take a look at a few sample problems. So suppose you're given the inverse cosine of the cosine of pi/6. The first question you would ask is this angle pi/6 in the domain of the restricted cosine function? If it is, these guys are going to undo each other. So in other words, is pi/6 greater than or equal to 0? Well, yeah, that part's true. And less than or equal to pi? Well, yeah, that's true as well. So I can go ahead and say that this would cancel away with this, and I'm just left with that pi/6. So that's going to be my answer. If you wanted to look at this on the unit circle, again, you would start, let's say we had the inverse cosine of the cosine of pi/6. And we're going to do this the long way. So we're going to start on the inside, and basically we would say, what is the cosine of pi/6? So I come to pi/6, that's right here. The x-coordinate is my cosine value, so that's square root of 3/2. So now we want the inverse cosine of the square root of 3/2. When I think about the inverse cosine function, again, I'm going to work from 0 to pi, where 0 and pi are both included. So I'm just going to ask the question, what angle has a cosine value of square root of 3/2 in this interval from 0 to pi, where 0 and pi are both included? Well, we already know that that's going to be pi/6. Here's your cosine value of square root of 3/2. So you're just reversing what you just did. You found the cosine of pi/6, and that was square root of 3/2. Well, now the inverse cosine of square root of 3/2 is going to get you back to pi/6. So this right here is your answer. And again, if you see something like the inverse cosine of the cosine of pi/6, because this pi/6 is in the domain of the restricted cosine function, or you could also say the range of the inverse cosine function, you can go ahead and just shortcut this process and say this is going to cancel with this, so they'll undo each other, and you're going to be left with this pi/6 as your answer. Okay, let's look at another example. So here we have the inverse cosine of the cosine of 5pi/4. This is the one where a lot of people would make a mistake. So if you give the answer as 5pi/4, that is incorrect. In other words, you can't just cancel here, because this 5pi/4, if you go to the unit circle, that's going to be right here. So that is not within the domain of the restricted cosine function or the range of the inverse cosine function. Again, you're thinking about this from 0 to pi, where both 0 and pi are included. So what you have to do for this particular problem, you have to go about it the long way. So you have to say this is the inverse cosine of the cosine of 5 pi over 4. Okay, so what is the cosine of 5 pi over 4? Well, if I come over here, that's going to be the negative of the square root of 2 over 2. Okay, so now I have the inverse cosine of the negative of the square root of 2 over 2. Okay, so what is the inverse cosine of the negative of the square root of 2 over 2? So if this guy is negative, I want to be in quadrant 2, where cosine is negative, and I'm looking for where I have a cosine value of negative square root of 2 over 2. So that's going to be right here, and that's going to be at 3 pi over 4. So this would be equal to 3 pi over 4. Now, if you had gotten the inverse cosine of the cosine of 3 pi over 4, again, because this 3 pi over 4 is in the domain of the restricted cosine function, or you could say the range of the inverse cosine function, in this particular situation, you can cancel this with this. Those will undo each other. And then basically you're left with that angle of 3 pi over 4. When you get a situation like this, because this is not within the domain of the restricted cosine function or the range of the inverse cosine function, you have to do more work. You have to first evaluate the cosine of 5 pi over 4, which is negative square root of 2 over 2. Then you take the inverse cosine of negative square root of 2 over 2, and that's going to give you this angle in quadrant 2, which is 3 pi over 4. All right, let's take a look at one more of these. So here we have the inverse sine of the sine of 6 pi over 5. Now, when we get this problem, again, I'm always asking, is this guy going to undo this guy? In other words, are these guys going to cancel away and just give me 6 pi over 5 as my answer? And here you're going to say no, because for this to work that way, you have to have this 6 pi over 5 being in the domain of the restricted sine function or the range of the inverse sine function, and it's not. If you think about, let's say, the range of the inverse sine function, again, you're working from negative pi over 2 to pi over 2, so you've got to be there. When you think about 6 pi over 5, that's not directly on the unit circle. I've sketched it in. So let me put 6 pi over 5, and you might be scratching your head saying, well, where's that angle at? And you can do some analysis and think about, okay, well, it's going to end up being in quadrant 3. So I'm just going to write this one out, and I'll give you an easier way to do that by converting it into degrees in a moment. So this would be greater than pi and less than 3 pi over 2. So that tells me I have an angle in quadrant 3. So let me just put that this is in quadrant 3. Now, an easier way to do that, if you're struggling with that, you can always convert it over into degrees. Way easier to do. So I'm just going to say it's 6 pi over 5 times, I'm going to go 180 degrees over pi. And so basically the pi's are going to cancel. And so 180 divided by 5 is 36. And so you'd have 6 times 36, that's 216. And now this is in terms of degrees. So this is 216 degrees. So I think a lot of people will find this easier to work with. And also immediately you know that this is going to be in quadrant 3. Whereas with 6 pi over 5, you really have to think about it because it's in terms of radians. I've already sketched this in to help us out. So this guy in orange, which I'm not sure if it comes through so well, so I'm going to try to do a rough trace over what I did. So this would be your angle right here. So this is what I'm looking at. So that's my 6 pi over 5. Now I know that the sine of 6 pi over 5 is going to be negative because it's in quadrant 3. I also know that the reference angle is going to be pi over 5. And the way I figure that out is, if I'm in quadrant 3, I take my angle, which is 6 pi over 5, and I subtract away pi. So I'll do that as 5 pi over 5, and that gives me pi over 5. So this guy right here, this reference angle, so this piece right here, that's going to be pi over 5. Now, I know that sine is negative, again, in quadrants 3 and 4. So all I have to do is come over into quadrant 4 and find an angle with a reference angle of pi over 5. But again, I don't want to do this. I don't want this angle right here, because I want to rotate clockwise in quadrant 4 when I have a negative argument for my inverse sine function. So I want this guy right here. So I'm going to draw over this, maybe use a different color. So this guy right here, that is going to be negative pi over 5. So I've got my pi over 5 reference angle. So now I want to convert my problem over to where I use something that's going to be in the range of the inverse sine function. So let me get rid of all of this. I think we're ready to go. And all we have to do now is say that the inverse sine of the sine of 6 pi over 5 would be equal to the inverse sine of, again, I'm going to convert this over into an angle that's in the range of the inverse sine function. And so I'm going to say it's the sine of negative pi over 5. because again, the sine of 6 pi over 5 and the sine of negative pi over 5, those are both going to be the same value. They're both in quadrants where sine is negative, so they're negative in quadrants 3 and 4, and the reference angle is pi over 5 in each case. So all I have to do now is give my answer, as these guys are going to cancel, and I'm left with that angle, which is negative pi over 5. All right, let's take a look at a few examples where we're going to solve some trigonometric equations using inverse trigonometric functions and the cancellation properties that we talked about earlier. So suppose you had something like negative 5 plus 1/2 tangent of negative 2x plus 5 pi over 4, and this equals negative 11/2. Now we want to solve this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. Now earlier in this section, we talked about how we could solve equations of this form, but here we're going to use a different approach. So let me copy the problem. So negative 5 plus 1/2, and then we have our tangent of, this is negative 2x plus 5 pi over 4, and this equals negative 11/2. So let me go ahead and grab this real quick. Just remember the interval that we're solving over. I'm going to come here to a fresh sheet so we have a little bit of room to work. So the idea here is still the same. You want to isolate the tangent of something. In this case, it's negative 2x plus 5 pi over 4. So you want to isolate that on one side. You want a number on the other. So what I'm going to do is add 5 to both sides of the equation. So over here, this is going to cancel away. And I'm going to have 1/2 tangent of negative 2x plus 5 pi over 4. And this would be equal to, over here I have a negative 11/2, and then plus, for 5, let's write that with a common denominator. So let's multiply by 2 over 2. So this would be 10/2. And then now I can add negative 11 plus 10, that's negative 1, put that over the common denominator of 2. So this would give me negative 1/2. Now again, if my goal is to isolate this guy right here, I have to think about the fact that I have that 1/2 that's multiplying that. So to get rid of that, I'm going to multiply both sides of the equation by 2. And so this is going to cancel, and this is going to cancel. And so at this point, what I have is the tangent of this negative 2x plus 5 pi over 4. And this equals, over here I just have my negative 1. So here's where we're going to use our inverse tangent function and the cancellation property that we talked about earlier. So I'm going to take the inverse tangent of each side. So let's start over here. I'm going to say that I have the inverse tangent of this guy right here. So this would be the tangent of negative 2x plus 5 pi over 4. And then this guy over here on the right, you're going to do the same thing. So I'm going to take the inverse tangent of this negative 1. Now again, we have our property where we said that the inverse tangent of the tangent of x, in this case, x is just this guy right here. So this is what's on the inside. We would say that this is equal to x as long as x is greater than negative pi over 2 and less than pi over 2. So we're going to use this property here. And basically, we're going to say that this guy and this guy are going to undo each other or cancel each other, however you want to think about that. And so I'm just going to be left with this part right here. So I'm going to say this is negative 2x. Let me move this down a little bit more. And then plus 5 pi over 4. And this equals the inverse tangent of negative 1. Now, most of you know that's negative pi over 4. But just in case you don't, again, you can always go to the unit circle and think about these things. So for the inverse tangent function, again, you're working from negative pi over 2 to pi over 2 with those values being excluded. So I'm going to make sure that I stop a little bit short there. So those guys are not included. Again, the negative pi over 2 and the pi over 2. And you're just asking the question, where in this interval here am I going to have a tangent value that's going to be negative 1? Well, a lot of you can see that at 7 pi over 4, you have a sine value that's negative square root of 2 over 2 and a cosine value that's square root of 2 over 2. So if you had the tangent of 7 pi over 4, you're dividing opposites, so that's equal to negative 1. Now, we can't put 7 pi over 4 because, again, we have to rotate clockwise here. So you've got to go like this. So this would be negative pi over 4. And, of course, that's coterminal with 7 pi over 4. So the tangent of 7 pi over 4 is equal to the tangent of negative pi over 4, and that equals negative 1. So if I took the inverse tangent, so the inverse tangent of negative 1, that's going to give me this negative pi over 4. Okay, so coming back to this point, what we want to do is solve for x. So now I have this guy that I want to isolate. So let's subtract 5 pi over 4 away from each side of the equation. So of course this is going to cancel. And now I'm going to have negative 2x is equal to, let's write this as negative pi minus 5 pi over the common denominator of 4. So this right here, negative pi minus 5 pi is negative 6 pi. So this is going to be negative 6 pi over 4. Now to simplify this, if you think about 6 and 4, there's a common factor of 2. So 6 divided by 2 is 3, and 4 divided by 2 is 2. So let's go ahead and write this as negative 3 pi over 2. So this is negative 3 pi over 2. Now as a last step, again, I want to isolate x. So what I want to do is think about the fact that negative 2 is multiplying x. So you can divide both sides by negative 2. Or since you have a fraction here, it's probably going to be a little bit easier if you multiply both sides by negative 1/2. So multiply both sides by negative 1/2. So of course you could write this as negative 2 over 1. And this right here would cancel and become a 1. And so you would have x is equal to negative times negative is positive. And then basically you would have 3 pi over 4. So that is only one solution. And that's part of the issue with this technique here. So you have x equals 3 pi over 4. So let's go back up to the top. And let me write that x is equal to 3 pi over 4. So I know that this guy right here is in quadrant 2. You're going to find that you actually have a solution in quadrant 1, 2, 3, and 4 with this problem. And the way I know that is I would look at the period of this guy, so I know how often these solutions are going to repeat. Again, the standard period for tangent is going to be pi. So when you look at y is equal to the tangent of x, well, the period for that guy is going to be pi. But if you have y is equal to something like the tangent of bx, well, then the period is now going to be pi over b, but that's when b is positive. In this case, you're going to have a negative here, so you can adjust the formula and say pi over the absolute value of b. So for this case, you have this negative 2 that's multiplying x. So the period for this guy would be pi over the absolute value of negative 2, which would be pi over 2. So that's going to be the period. Let me get rid of this. So let me put this like this, and let me put that the period is pi over 2. And actually, let me grab this real quick. It's going to come down here to the unit circle and rewrite things. So x is equal to 3 pi over 4. Again, this is in quadrant 2, and I'm going to put that the period, so the period is pi over 2. I think you can do it on the unit circle the first time just so you can get a visualization of what's going on. So I know that solutions repeat every pi over 2. So here I'm going to be at 3 pi over 4. So what I want to do is actually subtract away pi over 2 and find my solution in quadrant 1. A lot of you know that's going to be pi over 4. Well, let's go ahead and do the work here. So we have 3 pi over 4 minus pi over 2. Let's go ahead and write this as 2 pi over 4. So we can have a common denominator. So minus 2 pi over 4. And so this would give me, again, pi over 4. So that's a solution in quadrant 1. Now, if I want the solution in quadrant 3, then what I would do is actually take my 3 pi over 4. So 3 pi over 4. And I'm going to add 2 pi over 4. And that's going to give me 5 pi over 4. So that's going to be right here. And then in quadrant 4, of course, it's going to be 7 pi over 4, but let's just go through it. We would have the 5 pi over 4, this guy right here, and we're adding our pi over 2, or 2 pi over 4. So we have 5 pi over 4 plus 2 pi over 4. So that's 7 pi over 4. So those are your solutions in that interval that I gave. If we have x being greater than or equal to 0 and less than 2 pi, well then x is going to be equal to pi over 4. And then you have 3 pi over 4. And then you have 5 pi over 4. Let me scooch this down a little bit. And then you have 7 pi over 4. Then in terms of the general solution, if you did want that, although it didn't ask for it, you could start with pi over 4. So start with something like pi over 4. And then you could just add pi over 2 to get to the next solution, and then add pi over 2 to get to the next solution, and then add pi over 2 to get to the next solution, and add pi over 2 to get to the next solution, and that will continue forever and ever and ever. So pi over 4 plus your pi over 2 times n, where n is any integer. All right, one thing that I find helpful, especially for beginner students, is to look at a graph of an equation after you solve it. So you can go to Desmos. So I would say that you have 1/2 and then tangent of negative 2x plus 5 pi over 4. And then you have this negative 5 here. So let me write minus 5. I'm going to add this to both sides. So I'm going to add 11/2 over here. And then this would be equal to 0 because I added it over here as well. So this right here, this negative 5, that's negative 10 over 2. So this is negative 10 over 2. And negative 10 plus 11 is going to be positive 1. So this right here would be plus 1/2. So the way you would key this into Desmos is you would say that y is equal to this. And of course, if I plug in a 0 for y, now I'm just finding my x-intercepts, or the x values that make the y value 0. So I have the graph set up for us. Again, this is y equals 1/2 tangent of negative 2x plus 5 pi over 4 plus 1/2. So if you want to key that into Desmos, again, if I plugged in a 0 for y, now I'm looking for the x-intercepts. So where are the x values that make the y value 0? And of course, you're going to see this is consistent with what we found. So here you have your pi over 4, your 3 pi over 4, your 5 pi over 4, your 7 pi over 4. So that's in the interval that we solved in from 0 to 2 pi, where 0 is included and 2 pi is excluded. And then you would continue with this pattern forever. So you can keep just adding pi over 2 to your solution to get to the next one. So 7 pi over 4 plus pi over 2, or you could say 2 pi over 4, that's 9 pi over 4, then 11 pi over 4, then 13 pi over 4, then 15 pi over 4, then 17 pi over 4, so on and so forth. All right, let's go ahead and look at another example. So here we have 40 sine of beta minus 3, then plus 1 is equal to 6. Again, we want to solve this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So we're going to have 40 and then sine of this beta minus 3, and then plus 1 is equal to 6. So let me go ahead and grab this. Let's come down to a fresh sheet here. And again, my goal to start is to get the sine of this beta minus 3 on one side by itself. So I want to isolate that. So in order to do that, I'm going to start by subtracting 1 away from each side of the equation. So this would cancel. And so now we're going to have 40, and I'm going to put times the sine of this beta minus 3, and this would be equal to 6 minus 1 is 5. Again, I want to isolate this right here. So you have 40 that's multiplying that. So all I'm going to do is divide both sides of the equation by 40. So of course, this is going to cancel. And now you're going to have the sine of this beta minus 3 is equal to, when you think about 5 divided by 5, that's 1, and 40 divided by 5 is 8. So this is 1/8. Now, I've got to get this guy by itself. And in order to do that, I've got to get rid of this guy right here. So I'm going to use my property from earlier. Remember that if you have the inverse sine, so the inverse sine of the sine of x, this equals x as long as x is within the domain of the restricted sine function. So we would say for x being greater than or equal to negative pi over 2 and less than or equal to pi over 2. So here I'm just going to take the inverse sine of each side and use this rule here. So let me actually get rid of this. And I'm going to say that I have the inverse sine of this guy right here. So the sine of my beta minus 3. And this equals, again, I'm going to do that over here as well. So the inverse sine of 1/8. So at this point, we know that this will undo this. So those are going to cancel, and I'm left with my beta minus 3. And this equals my inverse sine. So my inverse sine of 1/8. Now at this point, you can give one solution for beta. You could just add 3 to both sides of the equation. And so this right here is going to cancel. And you're going to say that beta is equal to the inverse sine of 1/8 and then plus 3. So this is only one solution. To get the other solution, what you're going to have to do is think about your angle in quadrant 2 that has a sine value of 1/8. So what do I mean by that? Remember that if you have the inverse sine of something that's positive, so this is a positive argument, you're going to get something in quadrant 1. And actually, you're going to get this angle right here. Let me try to trace over this as best as I can. So that angle right there, if you're working with radians, that's going to be, let me put the inverse sine of 1/8 is about 0.125 in terms of radians. If you want to work with degrees, it would be about 7.18 degrees. So that's going to be for that angle right there. Let me just put this in so everybody knows what that is. So this is going to be about 7.18 degrees or 0.125 radians. Now, where is the sine value also going to be 1/8? Well, again, in quadrant 2, where I have a reference angle of 7.18 degrees or 0.125 radians. So you want this angle right here as well. So this angle right here as well, which again would have that same reference angle. So if I go down like this would be about 7.18 degrees or 0.125 radians. Now, how do I get this angle right here? So this is the angle. If I look at it, well, all I have to do is take the straight angle, which is pi, and subtract away this part right here. So you could do that by saying that you have your beta is equal to pi minus the inverse sine of 1/8. So again, that's taking this piece out, and then plus 3 like that. So let me go ahead and grab this real quick. And so we have these two guys here, and basically all I'm going to do is combine them into one little nice solution. So I'll just put a comma here. You can also use solution set notation if you want. Now, if you wanted to give the general solution, then basically all you'd have to do is say this guy plus 2 pi n, where n is any integer, and then this guy plus 2 pi n, where n is any integer, because your solutions are going to repeat every 2 pi. Now, if you want, let me go ahead and grab this real quick. Let me paste this in. If you want to verify these solutions, again, you can sketch the graph of this guy. The way I would do it is, I would say that you have y is equal to 40 sine of beta minus 3, and then I would subtract 6 away from each side, so I would say minus 5. So basically, if you subtract 6 away from each side here, you would have this part right here is equal to 0. I'm replacing the 0 with y, so I can graph this guy. And again, if y is 0, you're looking for the value for beta, or you could put an x here if you want for graphing purposes. So you're looking for the value for x such that the y value is 0, so you're looking for the x-intercepts. Now, in terms of approximating this, again, the inverse sine of 1/8, that's going to be about 0.125. And then if you add 3 to that, you're going to get about 3.125. So let's say that beta is about 3.125. So if you key this into your calculator, you're going to get about 6.01, let's just say 6. So 6.016, like that. Let me just grab this real quick. So coming down to the graph, again, you can sketch this on Desmos. This is one of the solutions we found, so about 3.125. This is another one, so this is about 6.016. So that's all in the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. And of course, if you wanted other solutions, if you wanted to give the general solution, everything is going to repeat every 2 pi. So if you take this solution and you add 2 pi, you're going to get to this solution here. If you take this solution and you add 2 pi, you're going to get to this solution here. All right, let's change things up. And now we're going to look at some problems that involve solving equations where you have an inverse trigonometric function involved. So here we have 3/4 times the inverse cosine of x over 2, and this equals pi over 4. Now for this type of problem, what you want to do is isolate your inverse cosine function. So I want inverse cosine of, in this case, x over 2 on one side, and I want a number on the other. So let's go ahead and just copy the problem. So 3/4, I'm going to put times the inverse cosine of this x over 2, and this equals pi over 4. If I want to isolate this guy right here, we'll have 3/4 that's multiplying this guy. So what I'm going to do is multiply both sides of the equation by the reciprocal of 3/4, which is 4/3. Remember that a number times its reciprocal will always give you 1. So when I multiply 4/3 times 3/4, those guys are going to cancel and give me a big fat 1. So now the left side is just what I want. It's the inverse cosine of this x over 2, and this is equal to, over here, the 4's would cancel, and so you would have pi over 3. Now, at this point, you could probably solve this by inspection. You can just look at this and say, well, the inverse cosine of 1/2 would be pi over 3, so I know x is going to end up being 1. It's a really easy equation. But if you didn't know that, what could you do to get your solution? Well, there's 2 strategies you could use. The first thing is you can go back to what we talked about earlier with the cancellation property. So if you have something like the cosine of the inverse cosine of, let's just say x. Right now we have x over 2, but let's just say x. This would be equal to x as long as this guy is within the domain of the inverse cosine function. So as long as x is greater than or equal to -1 and less than or equal to +1. Now, we're just going to use that here, and then I'll show you an easier way to do it. So I'm going to take the cosine of each side. So the cosine of the inverse cosine of x over 2 is equal to, I'm going to take the cosine of this side as well, so the cosine of pi over 3. So at this point, I'm just going to cancel this with this. These guys will undo each other, and you're going to have x over 2 is equal to, the cosine of pi over 3 we know is 1/2, and at this point, you know that x is 1, right? The denominators are equal, so you could, if you wanted to, just multiply both sides by 2. Let's just go ahead and clear the denominators away to make this official. So this guy would cancel with this guy, and this guy would cancel with this guy, and you get x is equal to 1. An alternative approach, if you get something like this, let me get rid of this right here, is to do this in a simpler way. So you'll probably see this technique in your textbook. You know that if you have the cosine of pi over 3, you get 1/2. So this is the angle, this is the cosine value. Then you also know that the inverse cosine of 1/2, so that's the cosine value, this is going to give you the angle, again, between 0 and pi, where 0 and pi are both included, where that cosine value is 1/2, so this is pi over 3. So if I look at this, the inverse cosine of x over 2 is equal to pi over 3. Well, this is your cosine value, and this is the angle. So all I really have to do is say, well, that means that the cosine of the angle, pi over 3, is equal to, again, this is the cosine value. So this is x over 2. So you can kind of shortcut that process and just set it up this way, just using the basic definition for cosine and inverse cosine. So once I look at this, I know that the cosine of pi over 3 is again 1/2. So this becomes 1/2 is equal to x over 2, and that just becomes x is equal to 1. Now with these problems, I always suggest checking them. You'll get a lot of problems that they throw at you with no solution here, or they get really tricky. So always check your problems here. So what I would do is plug in a 1 for x and see if I get a true statement. So you get 3/4 times the inverse cosine of 1/2. Is that equal to pi over 4? So the inverse cosine of 1/2 is going to be pi over 3. So you would have 3/4 times pi over 3. Is that equal to pi over 4? Yes, it is. If you cancel this with this, you would have pi over 4 is equal to pi over 4. So x equals 1 is a valid solution. All right, so again, I'm going to recommend that in this particular section, you look at the graph of everything just so you can confirm things. So I went ahead and just rearranged the equation so I could get y equals 3/4 times the inverse cosine of x over 2 and then minus pi over 4. So the equation was 3/4 and then cosine inverse of x over 2, and that was equal to pi over 4. So I just subtracted pi over 4 away from each side. So that would give you minus pi over 4 like this, and that would be equal to 0. So again, all I'm doing is I'm plugging in a 0 for y, and I'm saying for which x value am I going to get a y value of 0? So where's the x-intercept? If you look at the graph, where you're going to see that occurs right here, where you have a 1 for your x value and a 0 for your y value, so the ordered pair 1, 0. And again, that just confirms our solution that x is going to be equal to 1. All right, let's take a look at another one. So here we have 1/2 times the inverse cosine of x over 4. This is equal to pi. So in this particular case, again, I'm trying to isolate the inverse cosine function first. So here, the inverse cosine of x over 4. So let me just write 1/2 times the inverse cosine of x over 4. And this would be equal to pi. Now, if I want to isolate this guy, I need to get rid of this 1/2 that's multiplying it. So I'm just going to multiply both sides by 2. And so we're going to see that this right here is going to cancel with this right here. So now I have my inverse cosine of x over 4. That's on the left. It's isolated. And this equals pi times 2 is just 2 pi. Now let's stop for a moment and think about this. Is there going to be a solution for x? Is there something that I can plug in there, divide by 4, and then take the inverse cosine of that and get 2 pi? No, because the range of the inverse cosine function is from 0 to pi, with 0 and pi both being included. So this right here is impossible. So we would say that there's no solution. Right? So there's no solution. Again, if you want to look at this graphically, if you started with 1/2 times the inverse cosine of x over 4, and again, this was equal to pi, so let's put equals pi. Well, I'm going to subtract pi away from each side, so now I'll have minus pi equals 0. Well, again, I'm just plugging in a 0 for y, and I'm saying for which x value am I going to get a y value of 0? So where would I cross the x-axis or get an x-intercept? And you can see that this graph does not cross the x-axis. Basically, it goes from here to here. It's never going to cross the x-axis, so there is no solution. All right, let's take a look at a problem that's a little bit more tedious. So here we have the inverse cosine of 3/5 minus the inverse sine of x, and this equals 0. So if you get a problem like this, what I would do is I would isolate the inverse sine of x. So in other words, right now you have minus the inverse sine of x. So I would add the inverse sine of x to both sides of the equation. So let me just show that real quick. So I'm going to add the inverse sine of x on the left, and I'm also going to add the inverse sine of x on the right. So this would cancel away. So what I would have here is the inverse cosine of 3/5 is equal to the inverse sine of x. So I'm actually going to write this one on the left. That's just my preference. So I'm going to write the inverse sine of x is equal to the inverse cosine of 3/5. Okay, I'm going to come down to a fresh sheet so we have a lot of room to work. So what I'm going to do is actually take the sine of each side. So I'm going to say that I have the sine of the inverse sine of x, and this equals, I'm going to take the sine of the inverse cosine of 3/5. When I think about taking the sine of, again, the inverse sine of x, these guys will undo each other as long as x is within the domain of the inverse sine function. So from -1 to +1, with both being included. So x is equal to the sine of the inverse cosine of 3/5. What is the inverse cosine of 3/5? Again, that's an angle in quadrant 1, because this guy is positive, where the cosine value is going to be 3/5. So what I can do is say that I'm going to let something like theta be equal to the inverse cosine of 3/5. So again, this angle theta is going to be in quadrant 1 because the inverse cosine of something that's positive is going to give me something in quadrant 1. So I'm going to say that theta is in quadrant 1. Additionally, we know that this right here is the cosine value. So I can say then that the cosine of this theta is going to be 3/5. So what am I really trying to find for x here? Well, it's the sine of, again, the inverse cosine of 3/5. Well, the inverse cosine of 3/5 is theta. So really, I'm just trying to find the sine of theta. So you could really write this as x is equal to the sine of theta. How do we figure out what the sine of theta is? Again, if I know the cosine of theta is 3/5, and I know theta is in quadrant 1, this is really easy to figure out. So this right here is your adjacent, and this right here is your hypotenuse. Remember, for cosine, it's adjacent over hypotenuse. Again, you could also say that this is your x over your r. For the sine of theta, this is going to be your opposite over your hypotenuse, or you could write that as your y over your r. Well, I know that the r, or the hypotenuse in this case, is 5, so I can just put that in there. And again, you could just use your Pythagorean theorem to figure out what y is, or the opposite. A lot of you already know it's going to be 4, because this is a 3, 4, 5 right triangle. But again, you can always make a sketch. Now, for this one, it's very easy, so maybe you don't need a sketch, but I'll just go ahead and make one for completeness. So the adjacent is going to be 3. So you could say this is your x here, so x is 3. Your hypotenuse is going to be 5. So I'm going to say this is your r is 5. And of course, the opposite, or your y, is going to end up being 4. But when we first solve the problem, we don't know that. So what you would do is say that you have x squared plus y squared is equal to r squared, just coming from the Pythagorean theorem. And so we know x is going to be 3. So 3 squared is 9. And then plus y squared. Again, at this point, y is unknown. And this equals, we know r is 5, so 5 squared is 25. So what I would do at this point is subtract 9 away from each side of the equation. This cancels. You get y squared is equal to 25 minus 9 is going to be 16. And at this point, I would say that y is equal to the principal square root of 16, which is 4. You would use the principal square root here because you're in quadrant 1 and y values are positive. So coming back here, this would be a 4. So x equals the sine of theta, and the sine of theta is 4/5. So you can just say that x is going to be equal to 4/5 here. Now, how would you check something like this? Remember that theta is an angle whose cosine value is 3/5 and whose sine value is 4/5. So coming back up here, again, if you plugged in a 4/5 there, you'd have the inverse cosine of 3/5 minus the inverse sine of 4/5. Does that equal 0? So essentially what you have is, let's just say this is theta. Well, this would also be theta. It's the same angle, right? So the cosine of this angle is 3/5, and the sine of this angle is 4/5. So it's just theta minus theta is equal to 0. So you get 0 equals 0. So this 4/5 is a valid solution for x. Again, you can always go to Desmos and verify this solution graphically. So if you do something like y equals the inverse cosine of 3/5 minus the inverse sine of x, again, if you plugged in a 0 for y, I'm asking for which x value am I going to get a y value of 0, and that's going to occur at 4/5, 0. So this right here is your x-intercept, again, where y is 0. So that confirms our solution that x is going to be 4/5. All right, now let's look at something that's very tedious overall. I'm just going to tell you that you're definitely going to get problems like this in your textbook, and they take quite a while to solve, especially if you're doing this the long way. I'll also tell you that for most of these problems, there's an associated identity that you can use to greatly speed up your work. I would suggest for the first few times that you solve this type of problem, that you do it the long way so you can get a full understanding of what's going on. And then later on, when you come across these problems again, you can just use the identities and go a lot faster. All right, so let's look at the inverse sine of x minus the inverse cosine of x, and this equals pi over 6. So what should we do first if we get a problem like this? Pick one of these guys. So it could be the inverse sine of x or the inverse cosine of x, and you're going to isolate that on one side. So in this case, I'm going to isolate the inverse sine of x, and to do that, I'm just going to add the inverse cosine of x to both sides of this equation. So I'm going to go ahead and show this as canceling. So now I'm going to write this as the inverse sine of x is equal to, over here I'm going to have the inverse cosine of x, and then plus pi over 6. Now I'm going to end up taking the sine of each side, but before I do that, let me just grab this real quick and let me paste this in. I want to write this in a way to where it's crystal clear what we're doing and what everything means. So I'm going to make a little substitution. You've seen me do that already. So the inverse cosine of x, we know that that's an angle from 0 to pi, where 0 and pi are both included, where the cosine value is x. So in other words, I can let something like theta, or in this case, let's just use beta. So let's let beta be equal to the inverse cosine of x. So then what I can say is that the cosine of beta is going to be equal to x. I know that in terms of beta, right now, just looking at this, beta is going to be from 0 to pi, where 0 and pi are both included. That's coming from the range of the inverse cosine function. So let me say that beta is greater than or equal to 0 and less than or equal to pi. So I'm just going to change this from the inverse cosine of x to beta. So I'm going to erase this and just put this right now as beta. Okay, let's put this over here like this. Now there's something else that you have to consider. Let me actually grab this and slide it down right here. If I have the inverse sine of x, that's going to give me something from negative pi over 2 to pi over 2, where both of those guys are included. So that tells me that this right here, this beta plus pi over 6, has to be greater than or equal to negative pi over 2 and less than or equal to pi over 2. I'm going to put this in terms of beta being in the middle of that guy. So to do that, I'm just going to subtract pi over 6 away from each part of this guy. Over here, let me just add negative pi over 6. That would be the same thing. So basically, this would cancel. And over here, I'd want to get a common denominator. So multiply this by 3 over 3. And over here, I'd multiply this by 3 over 3 as well. So I would end up with negative pi plus negative 3 pi over the common denominator of 6. So that's negative 4 pi over 6. So this would be negative 4 pi over 6. And of course, each guy here is divisible by 2. So 4 divided by 2 is 2. So this would be negative 2 pi over 6 divided by 2 is 3. So let me erase all of this and put this as negative 2 pi over 3. And let me erase this. And over here, let's think about what we have. So this would be 3 pi minus pi over the common denominator of 6. So this would be 2 pi over 6. So 2 pi over 6. Each is divisible by 2. So 2 divided by 2 is 1. 6 divided by 2 is 3. So this is pi over 3. So this is pi over 3. Let me actually write this up here. And I'm going to write this a little bit more concisely. And let me come back up here. And let me paste this in here. And I'm just going to arrow to that guy right there. So we know that both of these would actually have to be true. Because beta is equal to the inverse cosine of x, I know that beta has to be greater than or equal to 0 and less than or equal to pi. But then it would also have to be true that beta is greater than or equal to negative 2 pi over 3 and less than or equal to pi over 3 because of this right here. So the inverse sine of x equals this beta plus pi over 6. So what you actually have to do is put these two guys together using the keyword and. So you're trying to find the intersection of the two. So if you consider these guys together, so I'm going to use the keyword and here. So beta is greater than or equal to 0 and less than or equal to pi. So that would look like this graphically. So here's 0 and here's pi. Again, that's about 3.145. Let's just say it's about right there. So this would be about pi right there. So this is what that looks like if you were to graph that inequality. Then for this one, beta is greater than or equal to negative 2 pi over 3 and less than or equal to pi over 3. Well, let's say that this right here is about negative 2 pi over 3. And let's say that this right here is about pi over 3. Just in case you're curious, negative 2 pi over 3 is about negative 2 point, let's say 0.9. And pi over 3, that's about, let's say, 1.05. So graphically, this would look like this right here. So this right here, if you want to look at that inequality, so something like that. So if I want the intersection of the two, again, I'm looking for values that are going to work in both. In other words, it would have to satisfy this one and this one. So when I set that up, I'm running out of room, but let me just do it over here. I would say that beta is greater than or equal to what? Well, consider that over here, you have a 0, and over here, you have a negative 2 pi over 3. Well, it's got to be 0. It's got to be the one that's more restrictive or further to the right, because it's got to work in both. If I had a value that was, let's say here, that was to the left of 0, but to the right of negative 2 pi over 3, well, it would work in this one, but it wouldn't work in this one. So I'm going to have to choose 0 here. And then I say it's less than or equal to. Well, for this one, I want the one that's further to the left, right? Because it's going to be more restrictive and include fewer values. So I want the pi over 3. In other words, if I had something like, let's say 2, that was to the right of pi over 3, well, it works in this one, but doesn't work in this one. So it's got to work in both. So I'm going to choose pi over 3. Okay, let me come down here, and I'm going to paste this in. And I'm coming back to this in a second. And let me grab this, and let me come down here and paste this in. So we're going to need this identity. That's why I have that set up already. So what I'm going to do now is take the sine of each side. So I'm going to take the sine of the inverse sine of x, and this is equal to the sine of beta plus pi over 6. When I think about this guy right here, again, from the cancellation property that we talked about earlier, this will undo this as long as x is in the domain of the inverse sine function. So from -1 to +1, with both being included. So let's go ahead and say that x is equal to this guy right here. So the sine of beta plus pi over 6. Now, I'm going to erase this, and now we're going to use this sum identity for sine to simplify this. So what I'll do is say that this is x is equal to, again, if you have the sine of a plus b, it's equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. So this would be the sine of the first guy, which is beta, and then times the cosine of the second guy, which is pi over 6, and then plus the cosine of the first guy, which is beta, and then times the sine of the second guy, which is pi over 6. Now, I know most of you know this, but if you go to pi over 6 on the unit circle, the x-coordinate is the cosine value, so that's square root of 3 over 2, and the y-coordinate is the sine value, so that's 1/2. So coming back up here, I can replace the cosine of pi over 6 with square root of 3 over 2, and I can replace the sine of pi over 6 with 1/2. So this right here is 1/2. Now, we also know what the cosine of beta is. So the cosine of beta, again, is going to be x. So this right here is going to be x. All right, so we're just going to plug some things in. So we have x is equal to, I'm going to go square root of 3 over 2 times your sine of beta. And then plus, here you're going to have 1/2 times the cosine of beta, which is x. So this is just x over 2. So this right here is x over 2. Now you have a common denominator. So what I'm going to do is actually say x is equal to the square root of 3 times the sine of beta plus x over the common denominator of 2. So the question now is, what is the sine of beta? So that's the holdup. So what is the sine of beta? So again, this is the opposite over the hypotenuse. Do we know what the hypotenuse is? Remember, the cosine of beta is equal to your x over 1. Right? Because x can be written as x over 1, and this right here is your adjacent, and this right here is your hypotenuse. So I know the hypotenuse is 1, so let me put that there. Now, what about the opposite? Can I figure that out? Remember that we said that beta is greater than or equal to 0 and less than or equal to pi over 3. So I'm just going to sketch a triangle in quadrant 1, and it would look something like this. So your adjacent is just going to be x, your hypotenuse is going to be 1, and you're going to find through the Pythagorean theorem that the opposite is going to be the square root of 1 minus x squared. So again, if you want to go through this, let's say that we label this right now generically as y. So we would say that we have x squared. So I'm just calling this length right here x, so it's x squared. Plus, I'm going to have this guy right here. Let's call that y. So y squared is equal to this guy right here, your hypotenuse. We know that's 1, so 1 squared. You're going to solve this for y. So you're just going to subtract x squared away from each side of the equation. I'm just going to erase this. And then to solve for y, you want the principal square root of this guy right here. So 1 squared is just 1 minus x squared. And the reason for that is, again, your y value is never going to be negative because beta is greater than or equal to 0 and less than or equal to pi over 3. So you use the principal square root here. So this right here is what you're going to get for your opposite, the square root of 1 minus x squared. Let me actually move this over. I don't think it'll fit. I'm just going to say that this is the square root of 1 minus x squared. Let me make this a little bit longer here, so this is over 1. So what I would do now is plug this right here in for that sine of beta, and then we would just solve for x. What I want to do is say that x is equal to the square root of 3, and then times, again, for the sine of beta, I have the square root of 1 minus x squared. If you want, you can combine those now. I think it'll make it a little bit easier to understand. Again, if you have the square root of a times the square root of b, we know this is the square root of ab. So the square root of 3 times the square root of 1 minus x squared would be the square root of 3 times the quantity 1 minus x squared. And if you distribute that 3 into each guy, you would have the square root of 3 minus 3x squared. So again, 3 times 1 is 3, and then minus 3 times x squared, that's 3x squared. Let me make this a little bit better here. And let me erase this and also erase this. So then we would say plus, you have this x here, and then this is over 2. Now, I want to grab this guy right here, and let me come down to this sheet here. The reason I'm keeping this here is because we're going to end up squaring both sides of our equation, and we want to remember that our angle beta, which represents the inverse cosine of x, that is greater than or equal to 0 and less than or equal to pi over 3, so I know that my x values here are greater than 0. So just keep that in mind. So for this one right here, I'm going to multiply both sides by 2. Let me put a little border and section this off. So multiply over here by 2. And of course, this is going to cancel away. And so now we'd say that we have 2x is equal to the square root of 3 minus 3x squared, and then plus x. At this point, I would subtract x away from each side of the equation. And so this right here is going to cancel. So 2x minus x is x. So x is equal to the square root of 3 minus 3x squared. Now, I want to square both sides. So what that would give me, let me come down here a little bit, is x squared is equal to the square root of 3 minus 3x squared. And again, I'm squaring this as well. So just squaring both sides of our equation. And that's going to give me x squared is equal to, so you're left with that radicand there. So 3 minus 3x squared. Let me make this 3 a little bit better there. So at this point, I just want to add 3x squared to both sides of the equation. This is going to cancel. And so you have x squared plus 3x squared. That's going to give me 4x squared. And this equals, over here I just have 3. Now if you want to solve for x, you divide both sides of the equation by 4. This would cancel. You're going to get x squared is equal to 3/4. Now here's where we need to think. Remember, with the square root property, we would say that x is equal to plus or minus the square root of 3/4. So this turns into plus or minus the square root of 3. So the square root of 3 over 2. Do I need the plus or minus here? No, because again, I cut it off, but we said that beta, which was our inverse cosine of x, is greater than or equal to 0 and less than or equal to pi over 3, which told me that x is going to be greater than 0. So what this tells me is that I don't need the negative of the square root of 3 over 2. That guy is not going to work. It's going to be an extraneous solution. It's something that was produced because we squared both sides of our equation. So you just get x equals the square root of 3 over 2. All right, so for these problems, again, I always recommend you check them. So let's put x is equal to the square root of 3 over 2. Let's just make sure that it works. Again, if you were to try to check x equals the negative of the square root of 3 over 2, the extraneous solution there, it's not going to work. Remember that x values would be positive when we're dealing with this angle beta. So what I would think about here is, what is the inverse sine of this square root of 3 over 2? A lot of you know that it's going to be pi over 3. But we'll go to the unit circle and grab it. And then what is the inverse cosine of square root of 3 over 2? Most of you know that's pi over 6. So let's put this as pi over 3. Let's put this as pi over 6. Let's go to the unit circle real quick, just in case you need it. So again, for the inverse sine of square root of 3 over 2, I'm working from negative pi over 2 to pi over 2. And I'm looking for a sine value of square root of 3 over 2. So that's going to be right here. And the associated angle, again, in this interval from negative pi over 2 to pi over 2, is going to be pi over 3. So that tells me that the inverse sine of the square root of 3 over 2, again, is pi over 3. And then for the inverse cosine of the square root of 3 over 2, again, with this one, now I'm working from 0 to pi. Both of those are included. So from 0 to pi. And again, where do I have a cosine value of square root of 3 over 2? Well, that's going to be right here at pi over 6. So this would end up being pi over 6. All right, so now let's just plug in. So the inverse sine of square root of 3 over 2 is pi over 3. So that is pi over 3. And then you'd have minus the inverse cosine of square root of 3 over 2. That's pi over 6. does this equal pi over 6? Well, if I get a common denominator here, I'd multiply this by 2 over 2. And so that would give me 2 pi minus pi over the common denominator of 6. Does that equal pi over 6? Yeah, 2 pi minus pi is pi. So this would be pi over 6 is equal to pi over 6, which is a true statement. So that solution x equals square root of 3 over 2 is a valid solution. Again, you can always verify this graphically. So you can set this up as y equals the inverse sine of x minus the inverse cosine of x minus pi over 6. Where did that come from? Again, if you have your inverse sine of x minus your inverse cosine of x is equal to pi over 6. Well, if you subtract pi over 6 away from each side of the equation, this would become minus pi over 6 is equal to 0. So all I'm really doing here is plugging in a 0 for y, and I'm asking for which x value am I going to get a y value of 0. So again, that's going to be your x-intercept. So here that occurs at square root of 3 over 2 comma 0. So that tells me the x value is square root of 3 over 2. So this confirms my solution that x equals square root of 3 over 2. In this lesson, we want to talk about solving trigonometric inequalities. All right, let's go ahead and look at the first problem. So this will be a really simple example just to get started. So we want to solve for x is greater than or equal to 0 and less than 2 pi. And so we have 4 minus the sine of x is greater than 7 halves. So how do we solve something like this? In this particular case, it's a very simple example. So you could isolate the sine of x on one side and then have a number on the other. And then you can go to the unit circle and get your solution that way. I'm not going to actually do that because I want to build up the concept that we're going to use for the harder examples. So what I'm going to actually do is make the right side 0 to start. So I'm going to say that I have, let's just reorder this, the negative of the sine of x and then plus 4. I'm just going to leave a space here and put this is greater than 7 halves. Now, if I want the right side to be 0, I just need to subtract 7 halves away from each side of the inequality. I would want a common denominator. So let me multiply 4 over 1 times 2 over 2. And let me put this minus sign down here. So at this point, I'm going to write that I have the negative of the sine of x. And then basically, this 4 times 2 is 8. So this would be 8 over this 2. So 8 over 2, that's the same thing as 4. We're just getting a common denominator. And 8 over 2 minus 7 over 2, we do 8 minus 7, which is 1, over the common denominator of 2. So that's just 1 half. So this is plus 1 half. And then this is greater than 7 halves minus 7 halves is obviously 0. At this point, what I would do is get rid of this negative that's in front of the sine of x. I'm actually going to write this as negative 1 times the sine of x, so it's crystal clear what we're doing. I'm just going to multiply both sides of the inequality by negative 1. Remember, if you do that, you have to flip the direction of the inequality symbol. So let me write negative 1 times this negative 1 times the sine of x, and then plus, you're going to have your 1 half times negative 1. This is going to get flipped. So right now it's a greater than. Because we're multiplying both sides by a negative, it's going to become a less than. And then you have 0 times negative 1. So negative 1 times negative 1 is positive 1. So this is just the sine of x now. And then you have 1 half times negative 1. That's negative 1 half. And then this is less than. 0 times anything is 0. So I'm going to grab this real quick. Okay, so at this point, I'm just going to come to the unit circle and put a little border here. Now this is an easier example. So of course, you could just figure out, well, where is the sine of x less than 1 half? Just by adding 1 half to both sides. I'm not going to do that because, again, I want to build up the method that we're going to use with the more challenging scenarios. But once you have everything down in terms of what method to use when, you can go ahead and solve it that way. It's no problem. So I'm going to write down that we want to find the critical values here. And how do we do that? Again, you replace your inequality symbol with equals. So you would have the sine of x minus 1 half is equal to 0. Add 1 half to both sides, and you get the sine of x is equal to 1 half. So basically, the solutions there, if we're working in that interval, let me write that out so we know, we're working from 0, and 0 is included, out to 2 pi, and 2 pi is excluded. Well, your solutions there, you're going to have pi over 6, you have a sine value of a half, and then also 5 pi over 6, you have a sine value of 1 half. So when I write down that the critical values are going to be where x is going to be pi over 6, and then 5 pi over 6. The reason we want to know that is we want to know where this guy right here, the left side of this guy, is going to be 0. So basically that acts as a boundary for us, and we're going to be able to set up some intervals on our number line, or you can also do it with a table, or you can do it on the unit circle. You could split this up and say, okay, well, one interval is going to be from 0 to pi over 6, and I'm going to exclude everything for right now. So basically you'd have an interval from 0 to pi over 6. So that's one of them. And then another interval, you would take from pi over 6, let me do this in a different color. So from pi over 6, and I'm going to exclude everything again. So pi over 6 to 5 pi over 6, both are excluded. So let me write another interval is pi over 6 to 5 pi over 6, both being excluded. And then a final interval here, you would take from 5 pi over 6 going to 2 pi, again, with both being excluded there. So let's say a final interval would be 5 pi over 6 going out to 2 pi, both excluded. And I have that written more neatly with a little table. Again, if you want to use a number line, it's really up to you. So all you have to do is pick something in each interval and test it and see if it works. So you can say true, false, something like that. You can also just figure out the sign. So basically, is it positive or is it negative? So coming back up, that's really easy to do. In this first guy here, so between 0 and pi over 6, is this guy going to be positive or negative? Well, basically, it's going to be negative. So let me put a negative sign there. And then between pi over 6 and 5 pi over 6, would this guy be positive or negative? Well, it would be positive. And then in this interval right here, between 5 pi over 6 and 2 pi, is it positive or negative? Well, it's going to be negative. So coming back, we want to put that it's negative here, it's positive here, and it's negative here. So if you want to put a solution together, you would say that it's going to work here, it's not going to work here, and it's going to work here. In other words, we're trying to figure out where is the sine of x minus 1/2 less than 0. So I'm trying to figure out where it's negative, because that would mean it's less than 0. So here it works. So let me put this in as x being greater than or equal to 0. I'm going to go ahead and include 0 because that's in the interval we're solving over. Again, when I set up my table, I exclude things just to make it simple. So x would be greater than or equal to 0, and you would have less than pi over 6. And then this part right here, it's positive, so we don't want that. Over here, you're going to have this interval. So 2 pi is excluded and 5 pi over 6, they're both excluded. So you're going to say x is greater than 5 pi over 6 and less than 2 pi. So just put this together. Let me slide down a little bit. So let me actually just grab this and move it here, and then grab this and move it here. And I'm just going to use the keyword or. That's all you have to do. Another way you can do this is you can put it in interval notation. So you can put a bracket with 0, and then you're going to go out to pi over 6, and that's going to be excluded. So you use a parenthesis, and then the union with, you're going to use a parenthesis with 5 pi over 6 because it's not included, and you're going to go out to 2 pi, and of course that's excluded, so you're going to use a parenthesis. So this would be your solution. X can be anything that's greater than or equal to 0 and less than pi over 6, or x can be anything that's greater than 5 pi over 6 and less than 2 pi. Okay, you can always look at these things on Desmos if you're a little bit confused or you want a visual confirmation of your solution. So we have y equals the sine of x minus 1/2. Remember, we were solving the sine of x minus 1/2 is less than 0. So all I'm doing here is asking where the y value is going to be less than 0, again, in that interval that I'm solving over. So if I look at 0, which is the start of the interval I'm solving over, you can see that you have a y value that's less than 0. So that's going to continue up to the point where you're not at pi over 6. So anything less than pi over 6. So again, that's where you get the zeros included up to and excluding pi over 6. Then the union with, if you look at anything greater than 5 pi over 6, 5 pi over 6 itself doesn't work because that's where you're at 0. But anything greater than 5 pi over 6 going up to and excluding 2 pi, because that's excluded from the interval we're solving over, that's going to work as well. So you'd put a parenthesis, and then again, 5 pi over 6, and then out to 2 pi with a parenthesis. Okay, let's take a look at a problem that's a little bit more challenging. So again, we want to solve for x is greater than or equal to 0 and less than 2 pi. We have negative 2 cosine squared x is greater than or equal to 1 plus 3 cosine of x. So again, I want to make the right side 0. In this case, I'm going to start off by actually making the left side 0 because it's easier, and then I'm just going to switch it around. So I'm just going to add 2 cosine squared x to both sides of my inequality here. So this right here would cancel and give me 0 on the left. So you would have 0 is greater than or equal to, let's write this out in front. So 2 cosine squared x, and then plus 3 cosine of x, and then plus 1. Okay, let me slide down here a little bit. Now, what I'm going to do is just rewrite this. So you can basically say that 2 cosine squared x plus 3 cosine of x plus 1 is less than or equal to 0. So that's how I'm going to set it up. If you want to solve it like this, that's fine as well. So I'm going to say this is 2 cosine squared x plus 3 cosine of x plus 1 is less than or equal to 0. All right, at this point, you want to find your critical values. So let me put a little border here and just say that we want the critical values. And again, how do we figure out what the critical values are? Well, basically, you replace this inequality symbol with an equal symbol. So I'm going to solve the equation 2 cosine squared x plus 3 cosine of x plus 1 is equal to 0. Now this guy is quadratic in form. So when you get something like this, generally speaking in a trigonometry class, you can factor it. Sometimes you do have to use the quadratic formula, but generally speaking, you're going to be able to factor. So let's go ahead and set this up because we can solve it with factoring here. So this is a 2, which is a prime number. That tells me this is 2 cosine of x, and this is cosine of x. So that's easy. The last guy here is a 1. And this guy is positive. So 1 is either 1 times 1 or negative 1 times negative 1. But because this guy is positive, I know this is a plus 1 and this is a plus 1. If you want to check it, you do your outer. So that's plus 2 cosine of x. And then your inner is plus cosine of x. So 2 cosine of x plus cosine of x is 3 cosine of x. So you're good to go with the factorization. So at this point, we would use the zero product property. So I would say that 2 cosine of x plus 1. So this factor here, set that equal to 0. Let's go ahead and solve that real quick. I'm going to subtract 1 away from each side of the equation. That cancels. You get 2 cosine of x is equal to negative 1. Divide both sides by 2, and you're going to get that this cancels. So the cosine of x equals negative 1/2. So let me write that the cosine of x is equal to negative 1/2. And then the other guy is the cosine of x plus 1 equals 0. So let me put or. We have the cosine of x plus 1 is equal to 0. You can subtract 1 away from each side of the equation. That cancels. So you get the cosine of x is equal to negative 1. So let me grab this real quick. And let me come down to the unit circle. So we should know these off the top of our head at this point. But just in case you don't, we know that cosine is negative in quadrants 2 and 3. And I'm just looking for where I have a cosine value of negative 1/2. So that's going to be right here. So there's your cosine value of negative 1/2, and that's 2 pi over 3. So then also here's 4 pi over 3, cosine value of negative 1/2. Then for cosine of x being equal to negative 1, well, I have a cosine value of negative 1 only at pi. So let me put here that we're solving over the interval from 0 to 2 pi. So that's clear. And then basically your solutions are x is equal to, you have 2 pi over 3, you have pi, and then you have 4 pi over 3. Now, these solutions are the critical values, and basically we're using this to split the number line up into intervals. So basically, I'm going to exclude everything here. I know a lot of people like to include 0 because it's included in the interval that we're solving over, but just to keep things simple, I am going to exclude everything, and then we'll put things together at the end. So for one interval here, I'm going to go between 0 and let's say 2 pi over 3. So that's one interval. Then another interval, so we're going to go between 2 pi over 3 and pi. And then another interval would be between pi and 4 pi over 3. And then for the final interval here, we'll say between 4 pi over 3 and 2 pi. So again, I'm not going to include any of those guys. Okay, so once again, I'm going to come to a little table. That's what I like to do to organize my information. So you saw that I set these intervals up on the unit circle. So I have between 0 and 2 pi over 3, then between 2 pi over 3 and pi, between pi and 4 pi over 3, and then between 4 pi over 3 and 2 pi. So when you're testing things, don't ever pick the critical values themselves. Just leave those alone. When we think about 0 and 2 pi, that's coming from our interval. So again, we're solving over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. And again, a lot of you are going to ask, well, why did I not include 0 here? You can if you want. This is personal preference. When I set this up, I just exclude everything. And then once I'm done and I'm putting the solution together, that's where I'm going to think about what's included and what's not included. So again, this is up to you. Let me drag this up here out of the way. And then basically, I'm just going to write my inequality. So we have two different forms we can use. So the unfactored form is 2 cosine squared x, and then plus 3 cosine of x, and then plus 1 is less than or equal to 0. So this is the form I would work with if I was using a calculator. Again, you could just pick something in each interval, plug it in, and see if it works. And then the form I would use if I'm not using a calculator is the factored form, because it's just easier to work with that if you're not using a calculator. So this was 2 cosine of x plus 1, and then times the quantity cosine of x plus 1. Okay, let me get rid of this unfactored form. Again, you can use that if you want. I'm just going to stick with this one. So we know that a positive times a positive or a negative times a negative is a positive. And we know that a positive times a negative and a negative times a positive would be a negative. I'm going to tell you that this right here, so this right here, this factor, based on what we can plug in, is always going to be positive. So I'm just going to put a plus right here. So basically, if this guy right here is negative, then the whole thing will be negative. And if it's positive, then the whole thing will be positive. Now, let me stop for a minute, because some of you will say, well, why is this factor always positive? I want you to think about the cosine function in general. So if you have the cosine of x, or you could write y equals the cosine of x, the range for that guy, as we know, is going to be from -1 to +1. And so you get this -1 here when you plug in a pi for x? Well, we can't plug in pi here because it's a critical value, so you're not going to be able to use that. So basically, when I think about the cosine of x, well, the smallest I can make this is if I plug in a pi for x and I get a -1, -1 plus 1 would be 0. But it's not going to be 0 because I can't actually choose pi, so it's going to have to be positive here. So I know that. When I look at this factor over here, now I have, let me put this as a little border, we have 2 cosine of x plus 1. So just ask yourself the question, where would it be negative? You can solve a very simple inequality for that. So just say, where is this less than 0? Subtract 1 away from each side of the inequality. That cancels. You're going to get 2 cosine of x is strictly less than -1. So this is less than -1. Divide both sides by 2. And so basically the cosine of x, if that's less than -1/2, then this right here would be negative. And so the whole thing would be negative. And this guy would be satisfied because if this side right here is negative or if it's 0, we'll have a true statement. So let's go back up and see where the cosine value is less than -1/2. So that looks like this interval right here. So that would make this negative, and then this interval right here. So right here, so that would make this negative. All right, so coming back to the table, we know that this guy right here would be negative, and this interval right here, so between 2 pi over 3 and pi, and then this interval right here, so between pi and 4 pi over 3. So let me put that in there. So we would satisfy our inequality there because this side right here would be negative, and that's always going to be less than 0. So in this interval here and this interval here, this factor would be positive, and so the whole thing would be positive, and so that's never going to be less than 0 or equal to 0. You can put a plus here and a plus here to show that. Okay, so to put the solution together, you would think about where this works. So because it's a non-strict inequality, and we allow for the possibility of this guy to be equal to 0, well, 2 pi over 3, pi, and 4 pi over 3, those are all going to work. So if you started off by just listing these in terms of the table, you could start with x is greater than or equal to 2 pi over 3 and less than or equal to pi, and then say or. You could look at this one. So you have x is greater than or equal to pi and less than or equal to 4 pi over 3. Now, of course, you wouldn't write it like this because of the keyword or. What's going to happen is this is just going to be x is greater than or equal to 2 pi over 3 and less than or equal to 4 pi over 3. So let me tighten this down like this. Let me get rid of that and put a less than or equal to here and just drag this over there like that. So this would be your solution. And if you want to list the interval notation, you're going to put a bracket next to 2 pi over 3, and you're going to go out to 4 pi over 3, and you're going to use a bracket there as well because both of these are included. So once again, if you want to look at this on Desmos, just to get a visual idea of what's going on, you can type in y equals 2 cosine squared x plus 3 cosine of x plus 1. And essentially we had the inequality 2 cosine squared x plus 3 cosine of x plus 1 is less than or equal to 0. So you're basically asking, where are the y values either 0, so at your x-intercepts, or less than 0? So if you look for your x-intercepts, again, we already know where that's going to be. You have your 2 pi over 3, you have your pi, and your 4 pi over 3. And then basically you're saying, where is it either there or less than 0? So you can sketch between these guys, and you're going to see it's going to be less than 0. So between those guys. So if you're looking for where it's either 0 or less than 0, you're going to take this section right here. So from 2 pi over 3 going up to and including this 4 pi over 3. So that's why we said the solution was, again, from 2 pi over 3 going up to and including 4 pi over 3. So that's going to be your solution in the interval that we're solving over from 0 to 2 pi, where 0 is included and 2 pi is excluded. All right, let's take a look at one more of these. So we want to solve for x is greater than or equal to 0 and less than 2 pi. We're given cotangent squared x minus 3 cosecant of x plus 3 is greater than 0. All right, so for this one, we're going to use a little identity to clean things up. You'll notice that the right side is already 0, so we're good to go there. One thing that I would note, if you're working with something that's not sine or cosine, you have to think about where your guy is undefined. So if you think about the cotangent squared x and the cosecant of x that you have, let's come down to the unit circle and remind ourselves, if you have something like y equals the cosecant of x, where is that undefined? Remember that the cosecant of x is equal to 1 over the sine of x. So basically, this guy right here cannot be 0. So where is your sine value 0? It's going to be right here at 0, and then right here at pi. So in the interval that we're solving over, the x cannot be the angle 0 or pi. because again, that would be undefined because you'd have division by 0. So let me put here that the domain, and typically we'll list this by saying that basically it's the set of all x such that x is not equal to pi n, where n is any integer. So 0, pi, 2 pi, 3 pi, something like that, because again, you get division by 0. Then if you think about the cotangent of x, so y equals the cotangent of x, and I know we have cotangent squared x, but basically you can extend this to that. Well, when we think about the domain here, so what is the domain here? Well, basically it's going to be the same, right? Because we have the cosine divided by the sine, and so the sine value cannot be 0. So that's going to happen at 0, then pi, then 2 pi, then 3 pi, so on and so forth. So basically it's the same thing. So it's the set of all x such that x is not equal to pi n, where n is any integer. Okay, now if you had, again, cotangent squared x, the same thing would apply because you're just squaring this, so you still can't have division by 0. So that would still apply there if you had y equals cotangent squared x. All right, let's get rid of this. We're going to say that at 0 and pi, this guy's going to be undefined. So I'm going to keep this highlighted for now. And actually, we might do better by just saying undefined. So undefined, and just putting a little note here. So I'm going to put 0 and pi, and that's going to be for in the interval that we're solving over. I'm just going to paste this in here, and I have a little identity set up for us already. So we know that the cotangent squared x is equal to cosecant squared x minus 1. So essentially, this right here matches this right here. So I'm just going to take this right here, and I'm going to plug it in for this right here. So that's all I'm going to do. So let's say that we have cosecant squared x minus 1. Again, this gets plugged in for this. Then minus 3 cosecant of x, and then plus 3 is greater than 0. So you have this negative 1 and then plus 3. So negative 1 plus 3 is positive 2. So let's go ahead and write this as cosecant squared x, and then minus 3 cosecant of x, and then basically plus 2, and this is greater than 0. So at this point, you would want to find your critical values. So the critical values, now this is quadratic in form, and you can solve it with factoring. So let's go ahead and replace this with equals. So you have cosecant squared x minus 3 cosecant of x plus 2 is equal to 0. Now, I would note that, again, with the critical values, you're also finding places where it's undefined. And we know that it's 0 and pi, like we talked about earlier. So you can throw that in the mix now, or you can put it in later, whatever you want to do. But I'm just going to put it in there now so we don't forget. So here what I want to do is factor on the left. So let me go ahead and set this up with some parentheses. Very easy to factor this. So this is cosecant squared x. So it's cosecant of x times cosecant of x. So very easy. This is 2, which is only going to come from either 1 times 2 or negative 1 times negative 2. This is negative right here, so this has to be negative 1 and negative 2. Let me make that a little bit better. If you check, the outer here is negative 2 cosecant of x. And the inner here is minus cosecant of x. Well, negative 2 cosecant of x minus cosecant of x is negative 3 cosecant of x. So this is the correct factorization. Okay, let me slide down here a little bit. And essentially, you want to find cosecant of x minus 1 equals 0. Add 1 to each side. You get the cosecant of x is equal to 1. Most of you know that's going to be at pi over 2, but we'll go to the unit circle in a moment. Then we have or. We have the cosecant of x minus 2 equals 0. Add 2 to both sides. So the cosecant of x is equal to 2. So that's going to be at pi over 6 and 5 pi over 6. Again, let's just go to the unit circle and let me paste this in here. So I have my undefined right there of 0 and pi just so we don't forget. So the cosecant of x equals 1. Again, if you don't know this, you can just convert it over into a sine problem. So we know that the sine of x is equal to 1 over the cosecant of x. So basically, the cosecant of x is 1. So this would be 1 over 1. So where is the sine of x equal to 1? Well, basically, you're going to be at pi over 2. That's where your sine value is 1. So for that one, you can go ahead and say that basically your x is going to be equal to pi over 2. Now, for the other one, you have cosecant of x equals 2. Again, you can convert that over into a sine problem. So you can say that the sine of x is equal to 1 over the cosecant of x. And the cosecant of x is 2. So the sine of x would be equal to 1/2. And where does that happen? Well, that's going to happen right here at pi over 6, and then right here at 5 pi over 6. Let me get rid of this. And actually, we don't need this anymore. We can actually get rid of this information. We're just going to list everything out. So from solving our equation, we have, and I can put this in order. So let's go pi over 6, and then we have pi over 2, and then we have 5 pi over 6. So this right here comes from solving the related equation. And then this right here, this comes from us determining where things are undefined, again, in that interval. So basically, you're going to split your, you could say number line or unit circle, again, however you want to think about that, up into different intervals. So you're going to have one that's between 0 and pi over 6. So that's going to be this part right here. So you think about something in there. And then the next guy would be between pi over 6 and pi over 2. So between pi over 6 and pi over 2. And then you're going to do between pi over 2 and 5 pi over 6. And then you're going to do between 5 pi over 6 and pi. And then you're going to do between pi and 2 pi. So that's the big one right there. In the previous example, you saw me use the factored form, but I'm just going to tell you for something like this is going to be very slow if you do that. So you can use the factored form and determine whether it's going to be positive or negative and do it that way. If I get this type of problem, personally, I'm just going to use a calculator. And so I'm just going to go through and set up a little table. This is how I like to do it. Again, nothing will be included here. So between 0 and pi over 6, between pi over 6 and pi over 2, between pi over 2 and 5 pi over 6, between 5 pi over 6 and pi, and then between pi and 2 pi. Now, I've already picked something to make this a little bit faster that's in that interval. You can pick anything in that interval you want. Just don't pick the endpoints themselves. Just pick something between. So I pick pi over 12 here, and you punch that into your calculator. You'll get about 5.34. Again, I'm rounding this. It doesn't matter. You're just trying to figure out if it's positive or negative, and so this is positive. So this guy, if you plug in pi over 3, you're going to get something that's negative, so about negative 0.13. So this is negative here. If you plug in the 3 pi over 4, you're going to get something that's about negative 0.24. So again, this is negative. Then if you look at 11 pi over 12, which would have a pi over 12 reference angle, you're going to see that you get that 5.34 again, so approximately, and this is positive. And then lastly, I'm going to pick this 5 pi over 4. If you plug that in, you're going to get about 8.24, so this is positive. So we want to know where this guy is greater than 0. So anywhere where it's positive, we're good to go. We have to be very careful about our endpoints here. So we know that they're not going to satisfy the inequality in terms of where this guy is 0, but you also have to worry about where things are undefined. So that's where this gets really, really tricky. So let me come down here and let me guide you through this so that you don't make a mistake. So you could say between 0 and pi over 6, this guy is going to work because it's positive. Do I want to include pi over 6? No, because that would make it 0. So that doesn't work because it's a strict inequality. Does 0 work? No, because that's where it's undefined. So again, normally you're solving from 0 to 2 pi, and basically you would include 0 and exclude 2 pi. But here, 0 is where you're going to be undefined, so you have to exclude that there. That's why I never include 0 when I do these types of problems, and people always complain, but then you run into a situation like that, and you maybe have 0 included or something like that, you're not thinking about it, and then you get the wrong answer. So that's why I exclude everything all the time. So basically for this one, you would say that x is strictly greater than 0 and less than pi over 6, so neither would be included. Skip this one and skip this one. Now you have between 5 pi over 6 and pi. Would 5 pi over 6 work? No, because it makes it 0, and that wouldn't be included. It's a strict inequality. Would pi work? No, because in this case, it's undefined at pi. So it's undefined at 0, pi, 2 pi, all those things. So basically, this is x is greater than 5 pi over 6 and less than pi. So it can't be pi itself. So then over here, you're going to have a positive again, but once again, pi cannot be included and 2 pi cannot be included. So you're going to say that x is greater than pi, and it's going to be less than 2 pi. Now, let me put the keyword or in here. I'm going to try to squeeze that in everywhere. And then let me come down here and write this more neatly in case you're trying to put this down for your notes. So basically, x is greater than 0 and less than pi over 6. Then you're going to say or. So you're going to say that x is greater than 5 pi over 6 and less than pi. Now, this is strictly less than here, so you cannot combine those two like a lot of people want to do. Pi cannot be included because it's undefined at pi. So don't put that in there. Let me come down here a little bit and say or. So we'll have another one of those. We'll say x is greater than pi and less than 2 pi. So that's kind of a lot. But when you solve an inequality like this, sometimes it gets ridiculous. And if you solve one that's harder, sometimes it gets really ridiculous. If you want to do the interval notation, it's not that bad. So you're going to say from 0 to pi over 6. Again, both are excluded. And then the union with, you're going to do from 5 pi over 6 to pi. Again, that's both going to be excluded. And then the union with, looks like maybe I can't fit this. Let me drag it down here so maybe I can fit it. So the union with down here, you would go from pi to 2 pi. Again, both are excluded. All right, so once again, if you want to go to Desmos and see this visually, you can type in y equals cosecant squared x minus 3 cosecant of x plus 2, and you'll visually be able to see all the things that I was talking about. So basically, you're asking, where's this guy going to be greater than 0? So where are the y values greater than 0? Well, if you start here at 0, notice that this guy can't be 0. because again, if you plugged in a 0 here, this is going to be undefined. So anything that's greater than 0 is going to work. And this is going to be going up to and then excluding this pi over 6. So when you hit pi over 6, this guy is actually going to be 0. So that would be excluded. So that's where you're getting that 0 to pi over 6 with both excluded part. And then the union with, if you look at it, here I'm going to be below 0, at 0, below 0, at 0. So once I get to 5 pi over 6, I know that's hard to read. That's another x-intercept that we found. And basically anything greater than that, going up to and excluding pi, we're going to be above 0 again. So we're going to say 5 pi over 6 going out to pi. But pi, of course, will not be included because you can see that this guy is going to have a vertical asymptote at x equals pi, right? These guys are going to approach an x value of pi, but it won't be able to actually touch it because it's undefined there. So then you have the union with, you would say anything that's larger than pi. So anything that's larger than pi, well, this is going to work again. You're going to be on this green graph right here, and this is going to work up into the point to where you get to anything less than 2 pi. So again, that's where you're undefined again. So from pi to 2 pi with both being excluded. So if you want to go to Desmos and check this out, you can visually see our solution. So anything between 0 and pi over 6. And then also you could say anything between 5 pi over 6 and pi. And then lastly, anything between pi and 2 pi. So all of those areas would work in the interval that we're solving over, which was from 0 to 2 pi, with 0 being included and 2 pi being excluded. In this lesson, we want to talk about the law of sines. And specifically here, we'll look at the easier case where we have angle, side, angle, and then also if we have the side, angle, angle. Okay, so before we jump in and look at problems, I want to talk a little bit about where the law of sines comes from. And so if you're not really interested in how this guy gets derived, you can just skip ahead to the examples. So the first thing is when we talk about solving triangles, earlier in the course we solved right triangles with the SOHCAHTOA, right? This just means we're finding all the missing sides and all the missing angles. Now, when we work with an oblique triangle, this is a non-right triangle, then basically we have to use something like the law of sines or the law of cosines because we don't have a right triangle, okay? So basically what I'm going to do is I'm going to start off with this acute triangle, okay, which let's just go ahead and call it ABC, okay? And I want to just draw your attention to a few things in terms of the naming conventions. So you see that you have capital letter A, capital letter B, and capital letter C. Those are your angles, okay? And then when you look at the lowercase letters, those are the sides, okay, that are across from their corresponding capital letter angle, right? So what do I mean by that? In other words, this is angle A. If I go across, I have lowercase a. This is for the length of this side here, okay? That's all that is. If you look at B here, this angle right here, if I go across, this is B, right? So it's the length of this side here, right? So on and so forth. You can do C as well. This is angle C. If I go across, okay, here's lowercase c here. So it's the length of this side. So you just need to understand how this is named because pretty much in every book, this is how they're going to do it. Now, what I'm going to do, because we have an oblique triangle, we're going to split this triangle ABC up into two different right triangles, okay? So you see I have this perpendicular here that's been drawn, and we've labeled this as H for the height, okay? You've seen this in geometry where you basically have the height so you can get the area, okay? So basically what we would do here is think about these two separate triangles. So I'm going to say I have triangle, and I'll call the first one ADB, so ADB. Okay, so if I think about that, that's A, D, B like this. So that's a right triangle now. And then I also have another triangle that I'm going to form inside. So let's call this triangle, okay? And let's go ahead and say this one's BDC. So let's say B, D, C. So B, D, C like this, okay? So you see the two right triangles. Now, let's think about, let's say, the sine of this angle here to start. So what is the sine of this angle A? Well, basically, I'm going to think about the opposite here, which in this case is H, right? If I'm thinking about this right triangle. So H over, what's the hypotenuse? Well, in this case, it's going to be C, right? Again, you might have to highlight this to really see. So this is ADB like this. If you think about this right triangle, this is your opposite and this is your hypotenuse. So this is H over C, okay? If you use a similar thought process, if you looked at C, okay, this angle here, what is the sine of this C guy? Well, now it's going to be the opposite, which is H, over the hypotenuse, which is A here, okay? So let's grab these two results, and let's just write this over here. So I have the sine of this angle A here was H over C, and then I also have the sine of this angle C is h over a, okay? What you're going to do is you're going to solve each one for h. So in other words, I would multiply this side by c and this side by c. And over here, let me make sure this is lowercase so I don't confuse anybody. Over here, this is going to be a, and this is going to be a. So you multiply both sides here by a, multiply both sides here by c. What's going to happen is this over here is going to cancel, okay? And this over here is going to cancel. So really, I can just erase this and say that h here is equal to c times the sine of a, and h here is equal to a times the sine of c. So since each one is set equal to h, I can set them equal to each other legally. So I can just erase this, and I can just drag this up here, or actually I'll put this over here to match the convention in the book. So let me write this a little bit bigger. So a times the sine of c, okay, is equal to, you're going to have c times the sine of a, like this. Okay, so what I want to do now is just divide both sides by the sine of a times the sine of c. So I'm going to divide this side by the sine of a times the sine of c, okay? And this side by the sine of a times the sine of c. So from here, I'm going to cancel this with this, and I'm also going to cancel this with this. And so what I get is, I get this a over the sine of a. Let me make that better. So let me make that better. So sine of a like this is equal to the c, okay, the lowercase c, is over the sine of c, okay, like this. So what this is telling you is that basically the lengths of the sides in a triangle are proportional to the sines of the measures of the angles opposite them. We could also do a similar process to show that a over the sine of a, okay, is equal to b over the sine of b. So I could say a over the sine, let me make this better. I'm trying to write this as small as I can. So sine of a is equal to b over the sine of b. And you could also show that b over the sine of b is equal to c over the sine of c. So I could also put c over the sine of c, okay? So you can go through and prove that to yourself if you want to go back to the triangle. But this is basically what we're going to be using throughout this lesson. It's very, very easy, okay, overall. You're just going to use one part. So in other words, you'll either use this guy right here, or you'll use this guy right here, or you'll use the original one we had, which is a over the sine of a is equal to c over the sine of c. Okay, so let's go ahead and jump in and look at an example. So we're given that b, which again, if you get a capital letter, this is an angle, is equal to 46 degrees, c is equal to 69 degrees, and a is 34 centimeters. So I'm going to tell you, like most people will, when you start these problems, just make sure you draw a little sketch. It doesn't matter if it's accurate at all. You just want something to put numbers down. All right, so I've already pre-drawn this little sketch for us. So you see that your angle B here is 46 degrees. Your angle C here is 69 degrees. And then this guy, if you go opposite of A, this is your A here, it's 34 centimeters, okay? So now if I think about what I need to find the measure of angle A. So let's go ahead and do that first. Remember, your triangle sum property tells you that the angles inside of a triangle are going to sum to 180 degrees. So on a calculator, you could go 180 degrees minus 69 degrees minus 46 degrees, and this is going to give you 65 degrees, okay? So you can go ahead and put a 65 degrees in there like that, okay? So that's what A is going to be equal to. Some teachers want you to draw this out, and some will say, okay, I want your answer, so we'll say A is equal to 65 degrees here like that. So we'll do both, okay? In terms of B, how are we going to figure this out? Well, you've got to work with what you have. So in other words, I have an angle measure A, and I have lowercase a, the side length, okay? So I can say that A over the sine of A is equal to B over the sine of B, okay? So I can just plug in for A here. This is 34 centimeters. So this is 34 centimeters. And then for the sine of A, you're taking the sine of 65 degrees. So the sine of 65 degrees. Then for this guy right here, B over the sine of B, well, B, the capital letter B is 46 degrees. So we're going to put 46 degrees there. And basically, if you want to solve this guy for B, right, lowercase b, you would say that lowercase b is equal to, you're just going to multiply both sides by the sine of 46 degrees. So you would say 34 centimeters times the sine of 46 degrees over the sine of 65 degrees. Now, if I punch that up on my calculator, I get about 26.9859, okay? Let's just go ahead and round this to the nearest tenth, okay? So I'm going to say that would be about 27. So let's just approximate this. I'm just going to erase all this. And I'm going to use the approximately symbol, okay? So I'm going to put approximately 27, okay? And this should be in terms of centimeters. So let's put this up here. So B is approximately 27 centimeters. And in terms of where you need a round, just get with your teacher or your assignment. It should tell you. Now, for C, the mistake that a lot of people make is they use this rounded value. You want to stick with the information you're given. You're given a hard-coded value here of 34 centimeters. Just use that again. So I'm going to want to do, and let me do this on another page. I'll do A, which is 34 centimeters, over the sine, okay, of A. Let me make that better. So the sine of A, which was, again, it's 65 degrees, is equal to, you're going to have lowercase c over the sine of, what was our angle C? That was 69 degrees, okay? So again, very easy to do overall. You're just going to multiply both sides by sine of 69 degrees. So you're going to have 34 centimeters times the sine of 69 degrees, okay, over the sine of 65 degrees. Okay, so this is what C is going to be. So let's erase this. So this would give me about 35.023, let's say 1. Again, if you want to go to the nearest tenth, we'll just say 35. So let's just erase this. We don't need it anymore. And we'll go back up and we'll say that this is about 35, okay, centimeters. So you can put this here. C is about 35 centimeters. So just depending on what your teacher asks for, you might want to list things like this. You might be asked to draw a triangle and then fill in the missing parts. Whatever it is, just make sure you have all the missing sides. Okay, here we got B is about 27 centimeters. C is about 35 centimeters. And then your missing angle, which here is 65 degrees. Okay, let's look at another one. Again, these are very, very easy. So A here is 52 degrees. B here is 67 degrees. And A, lowercase a, is 18 centimeters. So let's go down. And so again, A is 52 degrees, B is 67 degrees, and basically C is unknown. But again, we can find that really quickly. Just go ahead and do 180 degrees minus 52 degrees minus 67 degrees, and that's going to give you 61 degrees. Okay, so let's put that in there. So this is 61 degrees. And again, you might want to list this up here. So let's say C is equal to 61 degrees. And then we want to find B and C here. Okay, so I have my angle measure 52 degrees here for angle A, and then side A is 18 centimeters. So again, I can just set this up. I can say 18 centimeters over the sine of this angle A, which is 52 degrees, is equal to, let's just go ahead and start with B. So I'll say B over the sine of 67 degrees, okay? And if you haven't noticed, basically this guy right here always ends up being multiplied by this. So a shorter way to do this would be B is equal to, basically the sine of whatever this angle is times this ratio here, okay? That's all you need to do. So let's go ahead and say B is equal to 18 centimeters times the sine of 67 degrees over the sine of 52 degrees. Let me just erase this. So I get about 21.026, let's say 5, okay? And let's round this to the nearest tenth. So that's going to give us about 21. So let me erase this. And I'll say that this is about approximately 21. And don't forget your units, so we'll say centimeters. And again, I'll answer over here. So B is approximately 21 centimeters. Okay, for C, let's use a little shortcut. Okay, let's go ahead and say that C is equal to, again, I want this guy right here, 18 centimeters, okay, over this angle here, the sine of this guy, so the sine of 52 degrees. But I'm multiplying this by, again, remember you would have had C over the sine of C, which is the sine of 61 degrees, but we multiply both sides by that guy, okay, so we can clear it. So this is times the sine of this angle here, which is 61 degrees. Okay, no need to do two steps when you can do it in one. So if we go ahead and crank this out, you're going to get about 19.9784. Let's go ahead and round this to the nearest tenth. Let's just say it's about 20. Okay, so 20 centimeters. So let's erase this, and I'll say lowercase c here is approximately 20 centimeters. And again, you can write it in here if you want to, so 20 centimeters, okay? So we found C is about 20 centimeters, B is about 21 centimeters, and angle C here is 61 degrees. Let's just look at one more. So we have A is equal to 83 degrees, C is equal to 53 degrees, and lowercase c here, the side length is 8 yards. Again, we have our lowercase a, this side here we need to solve for, lowercase b, this side we need to solve for, and we don't know the measure of this angle B. I always start with the measure of the angle because it's the easiest. So you want 180 degrees minus 83 degrees minus 53 degrees, and that gives me what? Well, I would get 44 degrees. Okay, so this is 44 degrees. So let's erase this. Let's put B is equal to 44 degrees. Okay, so in this particular case, let's just go ahead and set up both of them really quickly. So we know we need to find this guy right here. So I'm going to use what's given here. I have this side C here, which is 8 yards, and I have the angle measure C, which is 53 degrees. So in each case, I'm going to use this ratio where I say 8 yards, okay, over, let's go ahead and say the sine of 53 degrees, okay? So if I wanted A, so A would be equal to what? It would be this times the sine of this angle here, okay? So the sine of this 83 degrees. Okay, so you set that one up. And then for B, B would be equal to, again, I'm going to keep this part the same, so 8 yards over the sine of 53 degrees. Let me make this better. So sine of 53 degrees, and then times the sine now of, in this case, the angle B is going to be 44 degrees. Okay, so 44 degrees there. All right, so let's start with A. Let's punch that up on our calculator. So if I round this to the nearest tenth, I'll just go ahead and say it's about 9.9. So 9.9, and this is yards, so I'll say approximately. Let's answer it twice. So here I'll put approximately 9.9 yards, and I'll do it up here as well. So A is approximately 9.9 yards. And then for this one, let's just go ahead and say that's about 7, right? Again, rounding to the nearest tenth, so it's about 7. So let me get rid of this, and I'll say this is approximately 7 yards. And then up here, B is approximately 7 yards, okay? So again, we found that A is about 9.9 yards, B is about 7 yards, and then this missing angle measure of capital letter B here is 44 degrees. Okay, so another thing you're going to see in this section is about the area of a triangle. So this is going to involve side, angle, side. So you're going to have two sides, okay, and the angle between them. So the method used to derive the law of sines can also be used to derive a little formula to find the area of a triangle. So I want you to recall from basic geometry, the area is equal to 1/2 times the base times the height, okay? So here our base would be this lowercase b, right? Because that's this side here, right? And then our height would be this h here, okay? This guy right here. So basically, I want you to think about our right triangle ADB again. Again, if we did sine of A, so sine of A, this is equal to, again, h over c. So h over c. Now, if I solve this for h, I'm going to get what? I'm going to get sine of A times c is equal to h. So sine of A times c is equal to h. So I'm going to plug this in right here into this formula, okay? So I'm plugging this in right there. So what I'm going to get is that the area is equal to 1/2 times the base times, instead of h, I'm going to have basically c times the sine of A. So let's erase this and put c times the sine of A, okay? Now, similarly, you could go through and calculate other formulas, okay, using a similar thought process. So you could say the area is equal to 1/2 times this. Now let's go A times B, okay, then times the sine of C. And then lastly, let's go area is equal to 1/2 times, let's see, what didn't we use? So it's going to be A times C and then times the sine of B, okay? So notice that this capital letter that's involved, okay, this angle, is always the one that's not involved here. I know these are lowercase, but if you look, you have lowercase b and lowercase c. This is uppercase A. Lowercase a, lowercase b, uppercase c. Lowercase a, lowercase c, uppercase b, okay? And that's because if you look at the way this is set up, if you have side B and side C, so this is side B, and this is side C, so where's the angle between them? Well, that's going to be this guy right here. It's going to be A, right? If I looked at A and B, so those sides, so this is side A, and this is side B, okay, what's the angle between them? It's going to be C. If I look at the last one, which is A and C, so if I look at A and I look at C, what's the angle between them? It's going to be B, okay? So this is a little formula you can use, okay, because in some cases, you're not going to know the height. You're not going to know what H is, okay? So you can basically use this instead. All right, let's look at this example here. So B here is 5 kilometers, A here is 10 kilometers, and C here is 121 degrees, okay? So again, you sketch yourself a little diagram, and basically we have, again, the side B here is going to be 5 kilometers. If I look at the side A here, it's 10 kilometers, and we know that C is 121 degrees. So again, you have this side here, you have this angle, you have this side here. Again, notice that the angle is between them. Okay, it's very important. So how do we do this? Well, again, we'll say the area is equal to, I'm going to go 1/2 times, again, you take these sides, so 5 kilometers, times, you're going to go 10 kilometers, so 10 kilometers, and then times, this is going to run off the screen, so let me drag this over a little bit. So then times the sine of the angle between them. So the sine of 121 degrees, okay? And so let's just go ahead and crank this out. And actually, since it doesn't fit on the screen very well, let me kind of simplify this here. So 5 times 10 is 50. 50 divided by 2 is 25. Kilometers times kilometers is going to be kilometers squared. So let me get rid of all of this and say that the area is going to be 25 kilometers squared, okay? And then basically times the sine of 121 degrees. So let's just go ahead and punch this up into our calculator. Just do 25 times the sine of 121 degrees. And I'll go ahead and say that's about 21.4. Again, if you're rounding to the nearest tenth. So the area is about, okay, approximately 21.4. And it's going to be kilometers. Again, this is squared. Very important that you square your units there because, again, you end up multiplying the kilometers times the kilometers, so you get kilometers squared. Okay, let me throw a wrench at you. So this is kind of a harder problem, a harder variation of this problem. So you have A is 11 feet, C is 69 degrees, and B is 76 degrees. So you've seen the pattern before with side, angle, side, right, where the angle is between them. But this one you have two angles and a side. So if I go down to my little sketch here, you see you have these two angles in this side here, okay? So basically, to solve this guy, to find the area, I either need to figure out C or I need to figure out B. Okay, it doesn't matter which one you do, you're going to get the same answer. But basically, if you had C, you have a side, an angle, and a side. If you had B, you'd have a side, an angle, and a side. So let's just go ahead and do B, okay? So we're given this 11 feet here. So to use the law of sines, I've got to first work with A, find the angle measure here. So that's going to be 180 degrees minus 69 degrees minus 76 degrees, which is what? Well, that's going to be 35 degrees. Okay, so this right here is going to be 35 degrees. So let's erase this, okay? So now again, if I'm trying to find this guy right here, I say that basically A, which is 11 feet, over the sine, okay, of A, in this case is 35 degrees, so the sine of 35 degrees is equal to, you'll have this lowercase b, again, it would be over the sine of 76 degrees, but we know we're just going to multiply this by this sine of this angle measure here, which is 76 degrees, okay? So basically, I'd have the sine of 76 degrees times 11 feet over the sine of 35 degrees. So that would be about 18.6, okay? So let me erase all of this, and I'm just going to say, and I'll just put this up here, that this guy right here is about 18.6, and this is in terms of feet. So now it's really easy to go back to our problem. We're going to say that the area, okay, is going to be equal to 1/2 times, again, I'm taking this guy right here, which is the 18.6, okay, feet, and then times this guy right here, which is the 11 feet, okay, and then times the sine of the angle, okay, between them. So in this case, it's 69 degrees. So times, let me do this down here, the sine of 69 degrees, okay? So let's just punch this into a calculator. So if I round this to the nearest tenth, I'm going to say this is about 95.5 feet squared, okay, or square feet. However you want to say that. So let's go ahead and say this is about 95.5 feet squared, or again, square feet, however you want to put that. In this lesson, we want to talk about the law of sines, where we have the ambiguous case. What's given is the SSA, or the side-side angle. All right, so in the last lesson, we talked about how to basically solve these oblique triangles. These are non-right triangles when you're given two angles in one side. So this could be angle side angle, which is ASA, or it could be side angle angle, right, SAA. Now, that's the easy case. You just go immediately into using the law of sines. Okay, you can just basically set up these proportions and you can solve for what you need to solve for. When you get to the ambiguous case, you're going to see side-side angle, and now you have to dig into the details of the problem. So before I get started into that, I just want to recap some things that we're going to need for this lesson. Some of you might find this quite boring, so you can just skip ahead to the examples, but I think you might find it quite beneficial. Okay, so first and foremost, let's revisit the law of sines. We have this a over sine of a is equal to b over sine of b, which is equal to c over sine of c. So we just write this in a compact form. You're only going to use two of these at once, right? So you might set these two equal to each other, like this, okay? If you're trying to solve for something in there, or you might set these two equal to each other, or you might set this one and this one equal to each other, whatever you need to do, okay? So you're basically only going to use two at one time. Now, alternatively, you could also write this like this. So you could say the sine of a over a is equal to the sine of b over b, which is equal to the sine of c over c. Now, really quickly, because I know somebody's going to be confused, remember we name the triangles, okay? Generally speaking, you'll see triangle ABC in your textbook. So capital letter A, capital letter B, capital letter C. Remember, those are angles, okay? The lowercase counterparts, in other words, if I think about capital letter A and lowercase a, the relationship is basically the lowercase letter is going to be opposite of the angle, okay, that's named with that capital letter. So you have capital letter A. If I look at lowercase a, that's going to be the side opposite of that angle, okay? It's going to be the length of that. If I look at lowercase b, it's going to be the side opposite of this angle, okay, with capital letter B. That's the name of it. Then if I look at lowercase c, it's going to be the side opposite of this angle named with an uppercase c or a capitalized c, however you want to say that. Now let's think about some of the properties for an angle, let's call it beta, of a triangle. Okay, so this is really important. When you think about the sum of the angles in a triangle, we know it's 180 degrees, okay? We know we can't have an angle in there that's going to be 0 degrees. It's going to be not possible. And also we can't have an angle that's 180 degrees. That's not possible as well. So we know that the sine of beta has to be greater than 0. Can't be 0 because, again, you can't have a 0 degree angle, okay? And you also can't have an angle that's 180 degrees. If we go back to the unit circle, remember, if you think about a sine value of 0, it's going to happen basically if your angle is 0 degrees or if it's 180 degrees, and I just said that's not possible, okay? So if we go back, we think about the next part of this, the sine of beta is, again, greater than 0 and less than or equal to 1. Well, remember, when you think about the sine, okay, we know the range of sine in general is from -1 to 1, but again, if you're working between 0 and 180 degrees, not including 0 or 180, well, then basically you're going to be between 0 and 1, where 0 is not included and 1 is, right? If you have a 90-degree angle, well, you can have a sine value of 1, okay? That means you have a right triangle. So let's go back. Here I said sine of beta equals 1. If this is the case, then beta is 90 degrees. Again, you have a right triangle. Lastly, we need to understand this because when we have two solutions here, this is going to come in. So remember the concept of a reference angle. If you have sine of some angle beta, let's call it 30 degrees. So sine of 30 degrees. This is equal to sine of 180 degrees minus 30 degrees, okay? 30 degrees here, if I take that away from 180 degrees, this would be 150 degrees. So this is sine of 150 degrees. We know this is true because of the concept of a reference angle. If you go back and you think about this, let me erase this highlighting here. If I had a 30-degree angle, the sine value is a half. If I had a 150-degree angle, okay, and I didn't draw that really well, so let me try that one more time. The reference angle there is 30 degrees, so the sine value is also a half, okay? Again, this is going to come up in a moment because we're basically going to be using the inverse to find our missing angle measure, and it might be possible that we have one that's, let's say, 30 degrees and another that's 150 degrees, okay? So we need to keep that in mind. Now, just a few other quick things about triangles that you may or may not know. Assuming the triangle has sides that are all of different lengths, the smallest angle is going to be opposite the shortest side. Let me highlight that. The smallest angle is opposite the shortest side. The middle valued angle is opposite the intermediate side. The largest angle is opposite the largest side. Okay, so you need to make sure you understand that because, again, it's going to come up today. All right, let's jump in now and look at some examples. I'm going to go through all the different scenarios and give you an example of each. So the first thing we're going to look at would be where there's no such triangle and you're given an acute angle. So we're given some acute angle A, and remember, opposite of A, we're going to have this side here, which is named with lowercase a. So we're given some angle A, and then opposite of that, we have some side A. These are both going to be given to us. We're also beginning given this side B here, okay? So the first thing you can think about, if you wanted to show that there was no such triangle, you could say that H is going to be greater than A, and it's going to be less than B, okay? So you could prove it this way. You could also show that the sine, okay, of this guy B, if you try to set this up with the law of sines, you're going to end up with something that's greater than 1. Okay, so I'll show you both for this example that's coming up in a minute. Now, you might be thinking, how in the world am I going to get h? So let's talk about that real quick. Let's get rid of this, okay? And let's think about if we formed a right triangle here, okay? And we thought about this angle A. Well, the sine of A is equal to what? It's the opposite over the hypotenuse. So in this case, because I formed a right triangle here, the opposite of it is h, and then the hypotenuse is b, okay? If you wanted to solve this for h, you would say that h is equal to b, okay, whatever this side is here, times the sine of a, the angle that you're given, okay? This is pretty easy to remember. Just going to erase this real quick and just drag this up here. Let me go down and we'll read off our problem, and we'll come back and we'll just kind of use this as a visualization of it. So we're given here that A is 61 degrees. So notice this is an acute angle, right? Then B is equal to 29 centimeters, and A is equal to 20 centimeters. So again, this is your angle here, and then this right here, because it's the lowercase letter counterpart, this is the side that's opposite of that, okay? So when we set this up, we'll say this is 61 degrees, okay? That's the angle you're given. Opposite of that, you have this side. Let's just go ahead and say again, it's A, so this is 20 centimeters. And then B, we're told this is 29 centimeters. So again, one way you can prove that there's no such triangle, you can basically plug into this guy right here, and you could say, okay, is H falling into this category? Is it greater than A and less than B? If it is, you can stop and say no such triangle, okay? So basically, I'm going to have B here, which is going to be 29 centimeters, so H is equal to 29 centimeters, times the sine of A, so the sine of 61 degrees. So this is going to be an approximation. So H is about, or approximately, we'll say 25.4 centimeters, okay? So you can see here that if I set up this inequality, I could say that 20 centimeters, which is A, is less than 25.4 centimeters, okay, which is H, is less than, you could say 29 centimeters, which is your value for B, okay? So we fall into this case here where we could say there's no such triangle, okay? It's not possible. The other thing you can do, and let me just erase this, if you wanted to do it this way, you could say basically that the sine, okay, the sine of this angle here, 61 degrees, okay, so the sine of A over A itself, in this case is going to be 20 centimeters, is equal to, again, the sine of this angle B over this B measure here, which is going to be 29 centimeters. Now you can multiply both sides by 29 centimeters. Let me just kind of slide this down a little bit. So we'll say times 29 centimeters over here. So we'll say this is equal to the sine of B. So the sine of B is approximately, let's just go ahead and say it's about 1.3 in terms of this guy. And again, the sine value is not going to be greater than 1. So that's another way you can prove that there's no such triangle. So however you want to do it, basically if you're going through the process of trying to solve the triangle and you get something that doesn't make any sense, it's just nonsense, you want to stop and say no such triangle, okay? So let me just put this over here and just say no such triangle. All right, let's look at another scenario. This is one where we end up having a right triangle. So basically here, you're going to see that this A value here is exactly equal to H, okay? So if A is equal to H, and then you could also say either A or H because they're equal, let's just go ahead and say A is going to be less than B, then we know that we have a right triangle. Now another thing here, since you notice you have B as a right angle, you could say that the sine of B, remember this is going to be equal to 1. So two ways to kind of check this. Let's go ahead and look at our example real quick. So we have A is 30 degrees, C is equal to 2 times square root of 5 inches, and A is equal to the square root of 5 inches. Now, instead of giving you a letter B, I gave you a letter C, just to throw a wrench at you. This is not any harder. If you want to work with this on this particular image, you just need to cross this out. Let me use a lighter color. You need to cross this out and put capital letter B, cross this out and put capital letter C, cross this out and put lowercase c, cross this out and put lowercase b, okay? Just adjust for what you're given. They're not always going to give you things in the exact format it is in your book, okay? So the first thing is, I want to prove that A is equal to H. How do I do that? Well, I'm given that A is equal to the square root of 5 inches. I'm given that, and I messed that up, I'm given that C is equal to 2 times the square root of 5 inches, okay? And I'm given that this angle A is 30 degrees. Now remember, for the height, we can say the sine of the angle A, is equal to, again, it's the opposite, which you could use as H here, okay, over the hypotenuse, which in this case we're going to use C, okay? So basically H is going to be C times the sine of A. So H, let me write this over here, h is going to be c, which we know is 2 times square root of 5, 2 times square root of 5 inches, times the sine of, in this case, it's 30 degrees, right? The sine of a. So what is the sine of 30 degrees? We all know from the unit circle it's a half. So let me put a little border here. H is going to be equal to 2 times the square root of 5 inches times 1/2, okay? My writing's getting a little sloppy here, so let me change that and put inches there so we know, or actually I can move this out to the end so that we don't have to mess with it for right now. We see this 2, we cancel with this 2, and basically h is equal to the square root of 5 inches. Well, what is a? Square root of 5 inches. So you've already shown that a is equal to h, and also you can see that a is less than b. In this case, we swapped b and c around. So again, you got to keep that straight in your mind. So this value here, okay, is less than this value over here. That's all you need to worry about. Now, in this particular case, you could also show that the sine of this angle, in this case it would be the angle C now, is equal to 1. So let's go down and think about this. So again, you use your law of sines. You could say that the sine of 30 degrees over this square root of 5 is equal to, you would have your sine of C over, you would have 2 times square root of 5, okay? So let's just go ahead and say this is a half. So I have 1/2, and then I'm dividing by square root of 5. So I'll just say down here it's 2 times square root of 5. Okay, so 1 over 2 times square root of 5, like this, is equal to, I'm going to multiply both sides by this. So I'm going to multiply both sides by 2 times square root of 5. And so look, this is going to cancel here with here, and this is going to be equal to the sine of C. So the sine of C is equal to 1, okay? So a little rough sketch of this if you want to look at it. Basically, if you want to find the rest of this, so you already know that C is a right angle, right? The sine of that guy is 1. We already know that opposite of that, where we're given that this is 2 times square root of 5 inches. We know A is 30 degrees, opposite of that, square root of 5 inches. So we need to find this and this. So where does that come from? If I want to find this 60 degrees here, the measure of angle B, again, what I want to do, if I come back up here, let me erase this. I would say that B is equal to 180 degrees minus 30 degrees minus 90 degrees, which is going to be 60 degrees, right? Remember, the 3 angles in a triangle have to sum to 180 degrees. So I can just take 180 degrees minus the measure of one angle minus the measure of the other angle. That gives me the measure of the remaining angle, right? Which in this case is B. So B here is equal to 60 degrees. Now, how do I find this lowercase b? How do I find this guy right here? And let me write in here that C is 90 degrees so we can solve this completely. Well, lowercase b is going to be found using, again, the law of sines. So I'm just going to go, in this case, I'll go square root of 5 inches over, I'll go the sine of 30 degrees. So I just did A over the sine of A is equal to, I'm going to say B, okay, B, which is unknown, over the sine of B. So the sine of 60 degrees. So the sine of 60 degrees. We know the sine of 60 degrees is square root of 3 over 2, right? So let me put this in here as square root of 3 over 2. And we know the sine of 30 degrees is a half, okay? So this is a half. Okay, so let's think about simplifying this a little bit. We know this would basically be 2 times the square root of 5 inches, okay, if I simplify that. So this would be 2 times the square root of 5 inches. Over here, this would be 2b over the square root of 3. So what I'm going to do, to get b by itself, I'm going to multiply both sides by the square root of 3 over 2. So this will cancel, and this will cancel, okay? And over here, square root of 3 over 2. So this is going to cancel. And basically, you get that b is equal to square root of 3 times square root of 5 inches, which I could write as a square root of 15 inches, right? So basically, b is the square root of 15, okay, inches. So let me erase this. And so now we've solved the triangle, right? We know all the sides and all the angles. Again, if you go back to this little picture here, or this little image, whatever you call it, again, this is 60 degrees, that's for b. And then the side opposite is square root of 15 inches. All right, let's look at another scenario. So this will be our third scenario. So here, you're going to see that basically your A is going to be greater than or equal to your B, and you're going to have exactly one triangle, okay? So you can also say that 0 is going to be less than your sine of this angle here, B, okay? Which is going to be less than 1, okay? It can't be equal to 1 because you don't have a right triangle in this particular case. Okay, so let's go ahead and look at an example. And so we have C is equal to 39 degrees, B is equal to 28 inches, and C is equal to 30 inches. Now, again, I switched the letters around on you. Don't freak out. So this is your angle that you're given. This side here, lowercase c, is the one opposite of that, okay? So you just plug back into the diagram that you're looking at. But for this one, you really don't need it. If you notice that this guy right here, okay, this right here is 30 inches. It's opposite of the angle you're given. If this measurement here, which is 30 inches, is greater than or equal to this measurement here, you know you're in the scenario where you're going to have exactly one solution. You can just start pounding away at it. Okay, you don't need to do anything else. So the first thing I'm going to do is I'm going to solve for my angle B. So let's start with that. So I'm going to say that the sine of B over B, okay, is equal to the sine of C over C, okay? And we know we can multiply both sides by B here, okay? So you can just get rid of this, and then I can just plug in. What is C? It's 39 degrees. Let me change my color here. So this is 39 degrees. What is lowercase c here? It's 30 inches. So this is 30 inches, okay? And then what is B here? It's going to be 28 inches, okay? If you want to cancel the units visibly, you can. So this is going to cancel. So basically, let me make this a little bit better. Okay, so this is 30 right there. Basically, you punch this into a calculator and you're getting an approximation. So you say sine of B is approximately, I'll say 0.5874. So 0.5874. And I'm using more decimal places here because I'm going to take the inverse, okay? So to find B here, you want to take the inverse of this guy, okay? So you could wrap this entire thing in parentheses here. So this entire thing here, plug it into the calculator, go sine inverse of that. Or you can do this way. You're going to be close enough. So I'll go ahead and say sine inverse of this guy right here, 0.5874, is going to be approximately, we round it to the nearest tenth, let's just say it's 36 degrees. So let's go ahead and say this is 36 degrees. And again, this is going to be my B here, okay? So let me erase all of this. And I will go ahead and say that B is going to be 36 degrees, okay? And this is approximately, so let me make the approximately symbol here. So then what is A? I'm solving for A here. Again, this is pretty easy. I'm going to do 180 degrees minus 39 degrees minus 36 degrees. This is going to give me what? So 180 minus 39 is 141. Take away 36, you get 105. Again, this is an approximation, okay? It's not going to be exact. So let's say this is approximately 105 degrees. And if I want the lowercase a here, again, I could just use the law of sines again. So again, go with what you know. So I'm going to go that 30 inches, which is this lowercase c, over the sine of 39 degrees. So the sine of 39 degrees, again, the sine of c, let me make that better. I'll say is equal to, you're going to have your lowercase a over your sine of 105 degrees. Again, I'm going to multiply both sides by the sine of 105 degrees, so I might as well just do it over here. So the sine of 105 degrees. So again, remember this is an approximation, so you can show that here if you want to, and say this is approximately a. Okay, most teachers will allow you to put equals there as well. And I'll go ahead and say this is about 46 inches. So let's say it's about 46 inches, okay? Now let me show you this sketch really quickly, and then I'm going to come back and show you why there can't be two solutions, okay, how you could prove this. So let me show you the sketch I made. So here you have your angle A, which is 105 degrees. Opposite of that, you have your side A, which is 46 inches. Again, this is an approximation. For B, it's 36 degrees. Opposite of that, okay, over here, you got 28 inches. And then C is 39 degrees. Opposite of that, you've got 30 inches, okay? So let's go back up. Let me show you why there can't be two solutions. We saw, let me just erase, or actually let me just box this off. We got an angle measure here of 36 degrees for B, okay, approximately, but let's just work with that. If we look in quadrant 2, and we think about, okay, what angle has a reference angle of 36 degrees? Again, we talked about this earlier. You would take 180 degrees, you would subtract away 36 degrees, and that would give you what? That would give you 144 degrees, okay? So remember, when you did that inverse sine operation, that's only going to give you something in quadrant 1 or 4, okay? We're working with positive values here, so you're always going to get something in quadrant 1. If you want to go into quadrant 2 and get something, okay, something that has the same sine value, in this case 144 degrees, you've got to use that concept of a reference angle. The problem here is that if I say that B could also be equal to this, even if it was approximately, well, we're given that C here is 39, right, degrees. So 144 plus 39 is going to give me 183. Remember the sum, and let me make that better, the sum of the three angles in a triangle is 180 degrees. So this is not possible. I can't have something that's 144 degrees because I'm going to go over, okay? So you can go ahead and exclude that right away. If you want to prove that to yourself, you can. But again, if you get an angle, in this case it was C, it's 39 degrees, and then the side opposite there, which is 30 inches, is bigger than this B that they're giving you, okay, the side in that position, which is 28 inches, you can go ahead and conclude that you're going to have exactly one triangle, and it's not going to be a right triangle in this case. All right, let's go ahead and take a look at one final scenario with given an acute angle and its side opposite. So you'll see this diagram or this image here is pretty busy. A lot of stuff going on because we're going to have two triangles here. So let me just quickly recap a few of the things that we've already seen. So we saw that if A was basically less than H and H was less than B, that there was no triangle, right? So there's no triangle in this particular case. But notice that A here is less than B. So this is kind of one of the things where you have to really be careful about what you're doing. Because if you see A is less than B, you could have no triangle, or if we're going to see in a second, you could have two triangles. Then we saw that if A was equal to H, okay, and you could say A or H, whatever you want to do, if A basically is less than B, then you would have a right triangle. And you would just have one, obviously, so one right triangle, okay? Then we saw that if A was greater than or equal to B, you would basically have, and let me not put a comma there, you would basically have one triangle. So one solution, one triangle. Here what you're going to see is that A is greater than H and it's less than B. So when this happens, you're going to have exactly two triangles, okay? So some students don't like to check things this way. They don't like to involve H, and you don't have to, right? You can always use your law of sines. So if you're using the law of sines with this guy, when you try to find the sine of the angle B, it's going to be greater than 1. Okay, so that's how you know you have no triangle. Here, when you try to find the sine of B, it's going to be greater than 0. So you can say it's going to be greater than 0 and less than 1. So this guy is going to give you your two triangles. This guy gives you your no triangle. Okay, so it's important to understand that. When we return here, let me go ahead and write this again. So A is greater than H and less than B. Okay, when we return here, A is going to be the same in each case. It's just how it's drawn. Okay, so you'll see this in your book, this little swing here. So basically the first way, you could draw a triangle this way, okay? So basically you'd have this B sub 1 here, that's your angle B. You have your angle C here, and then down here, I put C sub 1. Most books don't even put a C down there, but basically C sub 1 would be from A to B sub 1 like that. Okay, so the length of the entire thing, that would be your side C. Now, if we swing it this way, okay, and we draw this a different way, the length of A is the same. But now my triangle is going to look like that, okay, basically. And so when you think about C sub 2, now it's just going to be this short piece here, right? So that's my side C. So the angle C changed, okay, from basically here to just a smaller version, okay, and the angle B changes as well. So you're going to see the angle B change, the angle C change, and the side C change when you look at these guys and draw two triangles. Let's go ahead and look at an example here. So we have C is equal to 25 degrees, we have B equals 14 kilometers, and C equals 8 kilometers. So again, when I think about this, I have the angle and its opposite, okay? Don't worry about the letters. It's completely irrelevant, okay? Don't get hung up on that. If I want to find H, again, I'm using that same formula. Take this guy, okay? So this measure here that's not involved in the angle and its opposite, multiply by the sine of the angle you're given. It's all you're doing. So I'm going to take 14 kilometers, multiply by the sine of 25 degrees, and this is going to be equal to H, okay? And I like my variable to be on the left, so let's just go ahead and put it like this. So H equals this. We'll say H is approximately, let's go ahead and say 5.9 kilometers, okay? So if I think about this, is this guy less than this, okay, and greater than this? Yes, right? If I line this up, I would say 5.9 kilometers is less than 8 kilometers, okay, which is less than 14 kilometers. So I am in a scenario where I have two triangles, okay? That proves that. Now, again, if you just looked at this piece of information and this piece of information, you can only conclude that you either have two triangles or no triangles, okay? So you'd have to use the law of sines to get further into that. So let's go ahead and do that right now so we can start solving this guy. We know we're going to have two, okay? So I'm going to first start by finding my angle B, okay? So how do I do that? Again, I would say that the sine of C, okay, so the sine of 25 degrees, over C, which is 8 kilometers, then basically is equal to the sine of B over, okay, I'll go ahead and say this 14 kilometers here. Now I know I'm going to multiply both sides by 14 kilometers, so let me slide this down a little bit. And let me do this in a different ink, so I'll say 14 kilometers. We know that this is going to cancel here, and let me just erase it from here. So what would this give us? Well, you get about 0.739. Let's just go ahead and say 6. So I'll say the sine of B is approximately 0.7396, okay? So you want to use your inverse sine function, so I'll say sine inverse of this guy right here, so 0.7396. Again, if you wanted to wrap this guy right here, okay, inside the parentheses when you're doing sine inverse, that's fine too. Okay, this is going to be more accurate. Now, if I do this, I'm going to get about 47.7 degrees. So let me erase all this, and I'll say B, okay, B, and I'm going to put sub 1 is about, I put equals, so let me put approximately 47.7 degrees. Okay, so how do I get B sub 2? Remember, we talked about this earlier when we said we would use the concept of a reference angle. All we'd have to do is go into quadrant 2 and say, okay, well, 180 degrees minus this reference angle, 47.7 degrees, would give me 132.3, okay, degrees. So I'll say this is approximately 132.3 degrees, okay? Now I'm going to separate these two. I'm just going to put, maybe a border here or something like that, because we do need to find A, and you can put sub 1, and you want to put lowercase a here, sub 1, right? So this is all for the first triangle, okay? So I'm going to put approximately, and let's just erase this real quick, okay? So another thing here too, and I didn't do this, basically this is going to work because, again, when you add this, so 132.3 degrees plus this 25 degrees here, this is not going to be greater than 180 degrees. We saw earlier in the lesson we tried to add these guys together. We got 183 degrees, so it was greater than 180 degrees, so it didn't work. Here you have room for another angle because this is going to be 157.3 degrees, okay? So you see here for sure this is going to work and you're going to have two triangles. Okay, so let's erase this. Let me also add down here, I'll put A sub 2, okay? And I'll put lowercase a sub 2 like this. So let's work on this first one here. So if I want A sub 1, all I need to do is go 180 degrees minus 25 degrees minus 47.7 degrees. So this is going to give me, we'd say 107.3 degrees. So this is going to be 107.3 degrees. So let's erase this. And again, we're going to use our law of sines. So I'll go ahead and say that I have 8 kilometers over the sine of 25 degrees. So this is basically c over the sine of c. I'm going to multiply this by, in this case, I would have the sine of 107.3 degrees, okay? This will be equal to a. Again, if I did a over the sine of a, I would end up multiplying both sides by this. That's how I got that, okay? So if you punch this up on a calculator, we'll say this is about 18.1, and this is going to be in terms of kilometers. So we'll say 18.1 kilometers, okay? Let's erase this, and I'll quickly show you the sketch of this guy. So you see here, your angle A is 107.3 degrees. Opposite of that, I've got 18.1 kilometers. Your angle B here is 47.7 degrees. Opposite of that, I've got 14 kilometers. And then your angle C here is 25 degrees. Opposite of that is 8 kilometers, okay? So let's go ahead and look at the other guy. And again, we're going to solve things in a similar way. So now for A sub 2, I'm going to have 180 degrees. Minus 25 degrees, minus now 132.3 degrees. So this equals 22.7 degrees, okay? So let's put 22.7 degrees in like that. And now I just need A sub 2. So again, I'm just going to do the same thing. So I'm going to go 8 kilometers over the sine of 25 degrees times, in this case, I'm going to do the sine of this guy, so 22.7 degrees, okay? And this is going to be equal to A. So let's go ahead and punch this up on a calculator. And you're going to get an A is approximately 7.3, and this is in terms of kilometers. So 7.3 kilometers like this. So let's erase this. Again, I've drawn this triangle for us. So if we look at our sketch here, we have our angle A, which is 22.7 degrees. Then opposite of that, we have this 7.3 kilometers. Then we have our angle B, which is 132.3 degrees. Opposite of that, we have our 14 kilometers. Then we have our angle C, which is 25 degrees. Opposite of that, we have our 8 kilometers. So based on the information given, we can see that we can draw two different triangles. All right, so let's move on to the final two scenarios. These are pretty easy overall. This is when the angle you're given is now an obtuse angle. So basically, you just have two situations that deal with this. The first one is, let's say you have some angle A, it's obtuse, and you're given that, and you're given the side opposite of that, so this A here. If A is less than or equal to B, so if A is less than or equal to B, then you'll have 0 triangles. So 0 triangles, or you could say no triangle will exist. Let's look at an example. So here we have A is 125 degrees, B is 18 miles, and A is 14 miles. So again, this A right here is opposite of this angle A here, which is 125 degrees. By rule, a 125-degree angle in a triangle is going to be the largest angle. So therefore, it should be opposite the largest side, and it's not, right? This right here, this 14 miles, okay, is less than this 18 miles, so there's no triangle, right? No triangle exists. And I guess I could clean that up a little bit, so let's make that better. So exists. For the final scenario, we're given some angle A. Again, it's an obtuse angle. And we're given the side opposite, okay? And then we can basically say this side opposite A, in this case, is greater than B. So if A is greater than B here, so if this is greater than this, we'll have exactly one triangle. So let's look at an example. So here we have A is 114 degrees, C is 8 feet, and A is 35 feet. So clearly this right here, okay, which is opposite of this right here, is larger than this other guy you've got. So what I would do here is start by finding my angle measure C. So I would do the sine of C is equal to, let's go ahead and say the sine of 114 degrees, so the sine of A, over A itself, which is 35 feet, times it's going to be C, which is 8 feet. Okay, so remember, you divide sine of C by 8 feet, and then you multiply both sides by 8 feet, so that's how we set this up. So we know that this is going to cancel with this, and so basically what you'd have is about 0.20, let's say 88, okay? So let's say the sine of C is approximately, I'm going to say 0.2088, okay? So we're going to do the inverse sine, so sine inverse of this guy, 0.2088. This is going to be equal to, let's say, about 12.05, so maybe we'll go 12.1. So let's say that C, let's just erase this and put C, is approximately 12.1 degrees. Okay, so let's erase this. All right, so now let's go ahead and find my B. So this is approximately what? Well, I'm just going to do 180 degrees minus 114 degrees minus 12.1 degrees. And this is going to be equal to, let's say, 53.9, okay, degrees. So we'll say this is approximately 53.9 degrees. Okay, so we have that. And lastly, we just need this lowercase b, or this side measure. So let's go ahead and put this as approximately what? Again, I'm going to use the information I'm given. So I'm given A and then A here. So I'm going to say, since I want lowercase b, I'll say b is equal to, or put approximately, whatever you want to do. I'm going to say it's going to be this 35 feet, okay? So over, we'll do the sine of 114 degrees. So A over the sine of A. I'm going to multiply this by the sine of this b here. So the sine of 53.9 degrees. Again, we would have had b over the sine of b, so I just multiplied both sides by the sine of b. So that's how I got that set up, okay? So basically what I'm going to have here is, let's say, about 31 feet, okay? So let's say approximately 31 feet, okay? All right, so we've solved this triangle. When you get the obtuse situation, it's much easier. When you're dealing with an acute angle and the opposite side, okay, that's when you really have to dig into the details and really think. If you get an obtuse angle and its opposite side, that's pretty easy, right? You're basically going to say, okay, well, I have this one and this one. So is this one right here larger than this one right here that they gave me? If it is, you have one solution. If it's not, meaning they're equal or it's less, then there's no solution, okay, no triangle. So let's go down and look at a little sketch here. So I have angle A is 114 degrees. And again, opposite of that, you have the 35 feet. Angle B is 53.9 degrees. Opposite of that, you have 31 feet. Angle C is 12.1 degrees. Opposite of that, you have 8 feet. In this lesson, we want to talk about the law of cosines with the side angle side and the side side side. And also we'll look at Heron's formula for the area of a triangle. All right, so over the course of the last two lessons, we've been learning about how to solve these oblique triangles using the law of sines. So we saw the easy case with the two angles and the side given, angle side angle or side angle angle, okay? And then we saw the harder case, the ambiguous case of the law of sines, where we had to think about things, right? This is where we had two sides and a non-included angle, so side side angle. Now we're going to look at something that is a little bit different, right? So we're going to have side angle side, so two sides and an included angle, and then also side side side, right? So all three sides, no angles. When these two cases present themselves, we're going to be using the law of cosines now, okay? And we're going to say that a unique triangle can be determined. So we don't have to go through all this stuff that we saw with the ambiguous case of the law of sines. All right, before we get going on some problems, I want to give you some insight in terms of where the law of cosines comes from. I'm not going to go through deriving each one because there's going to be 3 of them, but I'm going to show you one of them and you can get the other ones on your own if you want. Now, some of you might not find this very interesting. Some of you might find it extremely boring. Just skip ahead to the problems if that's you, okay? So the first thing is, you'll notice that we have this triangle here, and it's an oblique triangle, and it's named ABC, okay? Typical. Now, you'll notice that we've put this guy on the coordinate plane, okay, where B basically is at the origin, right? So we have this 0, 0. You'll see for C, you have this A, 0. So where does this come from? Well, opposite of angle A, you have side A, right? Labeled with this lowercase a, right? So this is a length. You could think about this as the line segment BC, okay, right here, okay? Well, basically, this has a length of A, so the x-coordinate there would be A. The y-coordinate would be 0 because you're still on the x-axis, right? So that's where we get the A, 0 there. Okay. Now, up here, this one might be a little bit more confusing, but basically, to get this guy right here and this guy right here, you could start off by calling them x, y, okay? Just start with that generically. Then what you would do is you would take the sine of this angle B, okay? So how would we do that? Remember, this is an obtuse angle here. So what you do is you'd form this right triangle here, okay, like this, and you'd say, okay, the sine of B is going to be equal to what? It's going to be equal to the opposite, which in this case is going to be y, over the hypotenuse, which in this case is c. So y over c, okay? And then let's go ahead and do the cosine of this angle B also. Here you have the adjacent over the hypotenuse, so this is x over c. Okay, so far so good. Now where does this come from, this c times cosine of b and c times sine of b? Well, basically you're just going to solve for y and then solve for x and then plug in each case. Okay, that's all you're doing. So I'm going to multiply here both sides by c. So by c, and basically over here this is going to cancel, this is going to cancel. So y equals c times the sine of b, and here you see c times the sine of b, okay? And here x equals c times the cosine of b, and again, c times the cosine of b. So you're just taking what x is and you're plugging it in there, okay? You're taking what y is or what y is equal to and you're plugging it in there. So that's where all this stuff comes from. So let me erase everything. And now let's talk about a formula to find basically the length of this guy right here. So this would be using the distance formula. We know how to do this from basic algebra. But again, I'm going to call this side here b, right? Lowercase b, because it's opposite of angle b. So how would we do this with the distance formula? We would say what? Let's just write it here real quick. So we have d, the distance between these 2 points on the coordinate plane, is equal to the square root of, you have your x sub 2 minus your x sub 1 quantity squared, plus your y sub 2 minus your y sub 1 quantity squared. Okay, so from here now, what I want to do is I want to replace d with b, because the distance from here to here, it has a name, lowercase b. So let's put that in there, okay? And this is the square root of, again, it doesn't matter how you pick these points. I'm going to label this guy right here as x sub 2, y sub 2, and I'll label this one as x sub 1, y sub 1, just to make it easy. So I'm going to plug in c times cosine of b. So c times the cosine of b, and then basically minus a, this quantity will be squared, and then plus, we're going to do this c times sine of b, so c times sine of b, and then you would do minus 0. I mean, I can put that in there, but it doesn't really do anything, so I'm just going to close this and square it, okay? So let me copy this real quick, and let's paste this here so we have a lot of room to work, okay? So basically, the first thing you would do here, I mean, you could square everything inside first, but I'm just going to square both sides, and I'm going to say b squared is equal to, remove the square root symbol, so you're going to have c times cosine of b minus a, this quantity is squared, plus I'm going to have c times the sine of b, this quantity is squared. Okay, so basically what we want to do here is just expand everything, right? So this one right here, this is just multiplication. So you can just apply your exponent in each case, right? So this will be c squared times sine squared b, okay? But for this one right here, you have 2 terms, right? So you have to expand that or basically FOIL it out, right? In this case, it's a special product formula. So I'm going to have this as c squared, okay, first guy squared, times cosine squared b, okay? So this whole thing is squared, right? C is squared, cosine squared b, right? Because cosine of b is squared, okay? Then you'd have minus 2 times this guy times this guy. So 2 times c times cosine of b, then times a. Okay, if you want to write AC there, we can kind of rearrange that and make that a little bit cleaner. And then after that, you'd have plus the last guy, which is a squared. okay? So let me put all this together, and let's go ahead and say, don't forget this b out here, so I'm going to say this is b squared, okay, is equal to, this is going to be c squared times the cosine squared of b, and then minus we have 2ac times the cosine of b, and then plus a squared, and then don't forget about this one, so then plus c squared times sine squared b. Okay, so I can erase this at this point. I'm just doing that for kind of side work or scratch work, so I don't want that to confuse you, so I'm just going to get rid of it. Okay, let's move this up here. Now, one thing that might not be completely obvious, but you remember from probably earlier in the course, we saw something where we said sine squared theta plus cosine squared theta equals 1. You have a cosine squared b, and you have a sine squared b here, okay? So if I can get those two together, they're going to be equal to 1, okay? So this is what we're going to do. Let's go ahead and say we have b squared is equal to, I'm going to go c squared times cosine squared b, okay? And then I have this as a term here, this is a term, and then this whole thing is a term. So I'm going to put this over here. So plus c squared times sine squared b, okay? And then what didn't I use? I didn't use this, and I didn't use this. So let me put those after. So let me go plus a squared, and then minus 2ac times the cosine of b, okay? So some of you will see where I'm going with this. Others will be lost, and that's fine. I'll show you right now. Basically, what I'm going to do here is factor out the c squared, okay? So I'm going to have the b squared is equal to, we'll have this c squared out here, and then inside you'll have cosine squared b, plus sine squared b, okay, so that's taken care of. And then plus you have your a squared minus 2ac times the cosine of b, okay? So this right here we know is equal to 1, right, by definition. So you can erase this and just put a 1 in there, or just erase it all together because you don't need it anymore. So let's move this down here, okay, slide this down here, and basically you're done. So this is the law of cosine. So b squared is equal to c squared, then plus a squared, then minus 2ac multiplied by the cosine of b. Now, in your book, it's going to be rearranged. They'll put a squared here first, okay? And they'll put c squared here in the second position. But again, because this is just addition here, it wouldn't matter, okay? But this is how it's going to be listed in your book, so I want to be consistent. So where would this be useful? Let's go back up. I have things in terms of b squared, right? So if I knew my side A and my side C, and my angle here B, okay, my included angle, well then I could find the length of this guy B here, or the distance between these 2 points, using that formula, okay? Now additionally, we have 2 other forms, and I'm not going to derive this, obviously it would take forever, but you can do a similar process. So I'm going to do a squared is equal to, in this particular case you're going to have B and C now, so b squared plus c squared, and then minus, you'll have 2 times b times c times the cosine of a. Okay, and I think you see the pattern, right? So basically, you think about the side that you are solving for, it's the other 2 sides that you're going to need, right? So b and c in this case, and you get b and c here, and it's the cosine of the angle A opposite of this side A. And then the last one, you probably guessed it, so c squared is equal to, you're going to have a and b now, so a squared plus b squared minus 2 times ab times the cosine of, again, opposite of c would be big C, cosine of capital letter C, however you want to think about that. So to give a little summary of this little law of cosines, we're going to say that the square of a side of a triangle is equal to the sum of the squares of the other 2 sides. Then you could go less twice the product of the 2 sides and the cosine of the included angle. Okay, so this is a very easy pattern to memorize. Just go ahead and write it down in your notes. We're going to use it today. Okay, let's look at some examples here. I'm going to do 2 with side angle side and then 2 with the side side side. And then we'll look at some Heron's formula area problems. So the first thing you'll notice here is you have side angle side, right? So I have side B is 21 inches. I have angle C is 100 degrees. And I have side A is 27 inches. So let's go ahead and write this down. So we had B was equal to 21 inches, okay? We had A was equal to, it was 27 inches. And then we had angle C was 100 degrees, okay? So with this guy, again, what you're trying to do in this particular case, you're trying to figure out, when you start, what is the missing side, right? So what is this C over here? What is this? So equals what? So let's come back, okay? We're just going to plug into it. It's very simple. So c squared is equal to, hopefully you didn't forget this, so it's the two other guys. So it would be a squared plus b squared, okay? Then minus, it's 2 times this guy times this guy. So 2 times a times b, and then times the cosine of this angle here that you have. So the cosine of c, okay? Once you work with this a few times, it becomes very, very easy to remember it. And you're just going to plug in and basically hit this on a calculator and you're done, okay? So let me show you what you're going to plug in here and we'll approximate it together. You know that you want c by itself, okay? And c is going to be positive, right? So we don't need to consider plus or minus square root. So I'm just going to say c is equal to the square root of all of this, okay? So let me grab that, and I meant to just grab this part, and it doesn't seem to be doing that, so let me write it. A squared plus b squared minus 2ab, and then times the cosine of c. Okay, so c is equal to the square root of, let's plug in here. So for a, I'm going to plug in 27, okay? You can put the units in if you want or not. In the end, it's going to come out to just be inches, so I'm just going to leave them off, okay? Then plus, for your b, it's going to be, and I forgot to square this, for your b, it's going to be 21, so 21 squared, and then minus 2 times your 27 times your 21, and then times your cosine of 100, okay, degrees. Now, you're just going to punch this into a calculator, and I get about 36 point, let's say 97, and I'm going to do 37, okay? So I'm going to say my side c, okay, this is a lowercase c, is equal to 37, and then the units are inches, okay? All right, so let's erase this. And let's put here that c is approximately 37 inches. Now we need to find our two missing angles here, okay? And let's talk for a minute about using the law of sines or using the law of cosines. If you go back and you think about it, you can always, in any of these formulas, you can solve for this guy, okay? And you can end up using your inverse cosine function to solve, okay? So that's fine. If you want to use the law of sines, you have to be very, very careful. Why? Remember, if you have an obtuse angle and a triangle, you can only have one of them, okay? And it's going to be opposite the largest side. If we go back here, remember, assuming the triangle has sides that are all of different lengths, the smallest angle is opposite the shortest side, the middle valued angle is opposite the intermediate side, and the largest angle is opposite the largest side. Okay, so what am I getting at here? Well, basically what's going to happen is, in this particular case, you have an obtuse angle already, okay? So it is opposite of the largest side, and we can clearly see that. But let's say that you didn't have an obtuse angle. Let's say you had an angle that was like 30 degrees, for example. Well, when you go to find your other missing angles, if you're using the law of sines, you might run into a problem, okay? Because when you think about the inverse sine function, you can't get an obtuse angle out of that. Okay, you can't. You can only get something in terms of from quadrant 1 between 0 and 90 degrees. Okay, that's all you can do. So if you had something larger than 90 degrees, you would get the wrong answer, right? So for example, if the angle measure should be 110 degrees, if you plug in the inverse sine function there, you would end up with 70 degrees. Okay, that's just how it works. So what we do to fix this is we find the smaller of the two remaining angles using the law of sines, okay? Because if I find the smaller one, then it's not possible for it to be the obtuse angle because, again, a triangle can only have one obtuse angle. So if I'm finding the smaller one, it can't be that one. So I'm good to go to use the law of sines, okay? So let's go ahead and find the angle measure B, right? Because it's opposite the smaller side, right? This one's 21, this one's 27. Okay, so let's go back and let's go ahead and say that we have the sine of, in this case, C, which is 100 degrees, okay, over C, which is 37 inches, is equal to the sine of B over B is 21 inches, okay? So we already know how this is going to work. We're basically going to multiply both sides by 21 inches. So we'll say that the sine of B is equal to, we'll have 21 inches times, you're going to have the sine of 100 degrees. This is all over your 37 inches, okay? And you can go ahead and cancel the units inches out if you want visibly. Just punch this into your calculator, and you're going to find that the sine of B is approximately, let's just say it's 0.55, I'll just say 89, okay? So if you use your inverse sine function on this, I'll say sine inverse of this 0.5589. This is approximately, we'll say 33.98. So I'll round that to 34. So I'll say this is about 34 degrees. Okay, so that would be your measure for angle B. So let's erase all this. And I'll say that B is approximately 34 degrees. And then to find A, all you have to do is subtract, right? So you're going to do 180 degrees. basically minus your 100 degrees. Okay, so that would be 80 degrees. And then minus your 34 degrees, which would give me 46 degrees. Okay, so A is approximately 46 degrees. Okay, so we've solved this guy. Let's go back up, and I'll just say this is 34 degrees, and I'll say this is 46 degrees. All right, let's look at another example with side angle side. I'll go faster on this one. So basically here you have a side C that's 16 centimeters. You have an angle B that's 89 degrees, and you have a side A that's 28 centimeters. So let's say C is 16 centimeters. Let's say that angle B, sorry I was writing A, but angle B is 89 degrees. And then let's say that side A is going to be 28 centimeters, okay? So again, the first thing I want to do is find the missing side, right? So we're going to say B is equal to what? So again, just use your law of cosines, very easy. So we're going to say B squared, so B squared is equal to, again, which ones are not involved? So it's going to be A and C. So A squared plus C squared, and then minus 2 times A times C times the cosine of this angle here, which is B, okay? So we're just going to plug in. So let's just go ahead and say this is B is equal to the square root of, I'm going to plug in for A, that's going to be 28. And forget about the units, you don't really need them because it's going to end up just being centimeters. So then plus for the C, it's going to be 16. And then for the minus 2 times, again, it's going to be, and this needs to be squared, 2 times for this is going to be 28, and then times 16, and then times the cosine of, in this case, it's 89 degrees, okay? Let's punch this into a calculator. So I get about 32, let's just call it that. So I'll say it's about 32 centimeters. So we'll come here and we'll say that our side B is approximately 32 centimeters. And again, if we go back up here, we can just label this. I'll say this is approximately 32 centimeters. And again, you just want to take, out of these two sides here, you want to take the smaller side, okay, and then go opposite, and you want to find that angle measure. So I'm looking for angle C here because, again, it's not going to be obtuse. It's not possible, so I can use my law of sines. If you want to use the law of cosines, you can do that as well. It's up to you, okay? So let's go back, and let's figure out angle C. So I'm just going to say the sine of C is equal to, so I'm going to write 16 centimeters here. And again, you can leave the units off because you know you're going to end up canceling them out, but I'll just show it here. And then times, it's going to be basically the sine of 89 degrees, which is basically B, okay, over B, which is, in this case, 32 centimeters, okay? I'm going to visibly cancel these units, punch this into a calculator, and you'll see that the sine of C is approximately, I would say, 0.4999, let's just call it that. But if you wanted to make this a little quicker, you just take this whole thing, plug it into your calculator for the inverse sine function, and you'll have C, okay? I'm just doing this in 2 steps to make it a little bit easier to comprehend. So 0.4999, and then I'll say sine inverse of this guy, 0.4999 would be approximately, let's say it's about 30 degrees. Okay, so that would be for C. Okay, so let's erase this. So we'll say C is about 30 degrees. Okay, and then again, if you want to find A, you're going to do 180 degrees minus 89 degrees minus 30 degrees, which is 61 degrees. So I'll say that A is approximately, okay, I'll say 61 degrees. So we'll say this is about 61 degrees, and we'll say this one is about 30 degrees. All right, let's change things up just a little bit and look at the case where we have the side. So we have all 3 sides, and to solve the triangle, you need to find the 3 missing angles. So in this particular case, let me just read this off. We have our side A, which is going to be 17 miles. Let me make this equal sign a little bit better, okay? And then we have our side B, which is going to be 15 miles. And then we have our side C, lastly, which is going to be 28 miles, okay? So based on the information about a triangle that we know that this angle C here would be the largest angle, okay? Because it's opposite of this largest side, okay? So when you have all 3 sides, you're going to first find the largest angle using your law of cosines, okay? So let me grab this real quick. Let me cut it away. Let's come to a fresh sheet so we have a lot of room to work, okay? And I'm going to be focusing on finding our C. So what is this guy? What is the measure? So let's turn back to our law of cosines, and I'm going to use the one with the cosine of c involved. So in other words, let me just erase this real quick so I have some room. Let me box this off. I'm going to say, or actually I can actually do this up here. I'm going to say that c squared is equal to, remember, take the other ones that aren't involved. So you're going to have a squared plus your b squared and minus 2 times a times b, okay, times the cosine of c. So the idea here is that you're going to isolate the cosine of c, okay? So it's going to be equal to something, okay? You're going to be able to plug in for a, b, and c here, okay? And so then you can use your inverse cosine function and find out what c is approximately. Now, when you talk about the law of sines, again, with the inverse sine function, you run into problems because the inverse sine function is not going to be able to give you something in quadrant 2, right? So you're not going to be able to get an obtuse angle out of that. With the inverse cosine function, you can, right? It returns something from 0 to pi in terms of radians or from 0 to 180 degrees. So if you get a negative cosine value, you know you're in quadrant 2 and you have an obtuse angle. If you get a positive cosine value, okay, you're in quadrant 1, and so you have an acute angle, okay? Let's quickly solve this guy for the cosine of c. In the next example, I'll just give you the formula, but I just want you to see where this comes from in your book. So the first thing I would do is I would subtract a squared, and I would subtract b squared away from each side, okay? So minus a squared, and then minus b squared. So it's going to cancel over here. Let me write this down here. I'll say we have c squared minus a squared minus b squared is equal to the negative of 2ab times the cosine of c, okay? This is multiplication here, so what I'm going to do, to isolate this, I'm going to divide both sides by negative 2ab, okay? So divide both sides by negative 2ab. Let me erase this from up here so we can write this formula up here. This is, of course, going to cancel, so that's gone. So you'll have the cosine of c is equal to, you'll have your c squared minus a squared minus b squared over the negative of 2ab. Now, because this is a fraction, I can keep my negative down here, or I can get rid of it, and I can bring it up to the top like this, right? So I could distribute it to each part. So I could say this is negative c squared plus a squared plus b squared, okay, like this. And then I'm going to rearrange it. So I'm going to say, and this is how it's going to be in your book, so that's why I'm doing this. So the cosine of c is equal to, I'll say this is a squared plus b squared minus c squared all over 2ab. And I know it takes a while to get these things, and in tutorials we're used to just being given the formula, but I want you to see where things are coming from in your book so you're not always just getting things handed to you, okay? So let me grab this up here, and basically now I'm just going to plug in, okay? And to make this quicker, if you wanted to, you could just do the inverse cosine of whatever this is to give you c, right? So you could say c is equal to the cosine inverse of, so I'm just going to plug in for a, b, and c here. You can leave your units off. You know they're going to cancel. So a is going to be 17, so that's squared, plus b is going to be 15, that's squared, minus c is going to be 28, that's squared, all over 2 times, you're going to have your 17, and then times your 15, okay? So just punch this into a calculator, use your cosine inverse function, and let's say that's about 122 degrees, okay, if we round to the nearest tenth. So I'll say here that c is approximately 122 degrees, okay? And if you look at this value right here, you'll notice that this guy is negative, okay? So if the cosine value is negative, you're going to get an obtuse angle, right? Because you're getting something in quadrant 2. If this guy ends up being positive, you're going to be in quadrant 1, and you're going to have an acute angle, okay? But you see how you avoid that problem versus when you're working with the law of sines, right? There, you really have to be careful about what you're doing. So now that we have the largest angle, when I think about the angle A or the angle B, they have to be acute angles, right? If you always find the first angle as the largest angle, then you don't have to worry about the next 2 angles. You can just use the law of sines, okay? So let me get rid of this, and let's just use our law of sines here real quick. So I'm going to say, in each case, that I have the sine of, in this case, 122 degrees, over whatever c is, which is 28 miles. Again, you can write the units if you want. It's going to end up canceling. So I'm going to multiply this by, let's just start with a. We'll say it's approximately what? So let me go, the sine of a is equal to this. So I'm going to multiply this by what I would have divided by here, which is 17 miles, okay? So you can see that this is going to cancel here. Then to make this a little bit quicker, let's just go ahead and say a is going to be equal to, we're going to do our inverse sine function. So sine inverse of this whole thing, so the sine of 122 degrees over 28 then times 17, okay, like this. So if we punch that into a calculator, you're going to get about 31 degrees. So let's say A is about 31 degrees, okay? And then once you have those two, again, you could just use the angle sum property of a triangle. So again, 180 degrees is the sum of all the angles. And make that 0 a little bit better. Then minus, you've got this one as 122 degrees. Then minus, you got this one as 31 degrees. You can just say this is 27 degrees, okay? So this is about 27 degrees. So let's go back up, and I'll say C is 122 degrees. Again, this is an approximation. A is about 31 degrees, and B is about 27 degrees. Okay, let's look at one more example. I'll go a little bit quicker through this one. So we'll say A is 13 feet, okay? And then you could say B is going to be 29 feet. And then C is going to be 21 feet. Okay, so let me grab this and let's paste this in. Again, you're going to work with your largest angle first. So look for your largest side. So that's going to be here, right? So we're going to be looking for B. So I'm just going to give you this formula. Again, if you wrote out the B squared is equal to A squared plus C squared minus 2 times A times C times the cosine of B, okay? And you solved it for the cosine of B, you're going to end up with the cosine of B is equal to, we'll say A squared plus C squared minus B squared all over your 2AC. Okay, so let's get rid of this. And again, if you really wanted to take this forward, you could say that B is equal to the cosine inverse of, you can just grab this right here. So A squared plus C squared minus B squared over 2AC. Okay, so you can just plug in like this and basically find out what B is approximately. All right, so let's plug in. For A, we have 13 feet. So we have, let me change colors here. We have 13 feet. I'm just going to put 13. Forget about the units. So for C, I'm going to put 21. So put 21. And then for B, I'm going to put 29. So let's put 29 there. And then 2 times A times C. So A is 13. And C is going to be 21. Okay, so let's punch this into the calculator. And I get about 115 degrees. So B is approximately 115 degrees. Okay, let's erase this. And again, I've got my obtuse angle. Okay, so once I have my obtuse angle, the other ones are going to be acute for sure. Okay, so I don't have to worry about the law of sines, right? It's not going to give me an error if I use that now. All right, so let's solve for A. So we have the sine of A is equal to, we go A, which is basically 13 feet, times, let me make that 3 a little bit better, times, we're going to go the sine of B, so the sine of 115 degrees, and this is all over B itself, which is 29 feet. Now, we're going to end up taking the inverse of this, so you might as well say that A is equal to, let me slide this down, A is equal to the inverse sine of this guy right here. Okay, so let's punch this into the calculator, and let me visibly cancel these units. And you'll get about 24 degrees. So I'll say A is approximately 24 degrees. So let's erase this. And then again, for C, all you have to do is do 180 degrees minus 115 degrees minus 24 degrees. And that's going to give me 41 degrees. Okay, so this is about 41 degrees. So let's go back up, and we'll say B is about 115 degrees, A is about 24 degrees, and C is about 41 degrees. All right, let's talk about this Heron's formula and how to find the area of a triangle given the 3 sides. So side, side, side. You can also use this with side, angle, side. Okay, and I'll show you that in a moment, but it's much slower than the formula we saw with the law of sines. Okay, so with this guy right here, I'm given that basically, let's say side A is going to be, so A is 10.7 meters. Then let's do side B. That's going to be 9 meters. And then side C is 10. Let me put the C there. So C is going to be 10.5 meters. Okay, so let me grab this, cut this away, bring this over here. Let me paste this in here. Okay, and let me give you a little formula. Okay, so for Heron's formula, basically the first thing is you're going to find the perimeter of the triangle and divide it by 2. Okay, in your book, you're going to see this called S. So S is equal to, you could say 1/2 times, you sum the sides. So A plus B plus C. Okay, you know how to get the perimeter of a triangle. So in this particular case, S would be equal to, we'd have 1/2 times, your A is 10.7. I'm going to leave the units off for now. So 10.7 plus 9 plus 10.5 is 30.2. Okay, so this would be 30.2. You can put meters in there if you want. It's up to you. And then basically I would divide this by 2, so you could say S is 15.1, okay? So let's say 15.1, again, if you want to put meters there, you can. In the end, you know with area, it's whatever units you have squared, okay? So if you want to work with that, that's fine. So then from here, what you're going to do is you're going to plug into this kind of long formula. So the area is equal to the square root of, you're going to take this s and you're going to multiply it by your s minus your a, then your s minus your b, okay, then your s minus your c, okay? Very easy formula to remember. So basically, if I plug in here, I would say the area is equal to, and again, I'm going to leave the units off to make this shorter. You would end up with meters, 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 so meters to the fourth power. When you take the square root of the fourth power, you get the second power, or squared, which we know from an area formula, that's what you get, okay? So you're going to end up with meters squared, so I'm just going to tell you that in advance, okay? So basically for s, this is going to be 15.1, then times, you would do 15.1 minus 10.7, which is 4.4, okay? Then s, which is 15.1 minus b, which is 9. So that's going to give me 6.1, okay? And then s, which is 15.1 minus your c, which is 10.5, which would give me 4.6. Now, of course, you don't have to set it up this way. You can just punch it straight into the calculator. I just wanted to give you a little insight into what's happening. So I'm just going to crank this out in the calculator and see what I get. So I get about, let's say, 43.2 if I round it to the nearest tenth for the area. Okay, so I'll say the area of that triangle, we'll say is approximately, I'll go 43.2. Okay, let me slide this down. Don't forget your units. You want to put your meters squared, because again, if you had meters here, 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 and here, okay, you would have had meters to the fourth power. When you take the square root of that, you would have got meters squared. Okay, so that's where that comes from. All right, let's look at another example. So this is side angle side here. So basically with this one, it's going to be faster using that area formula with sine. So with that one, let me just copy this down. So C, let's say C is 5 meters. We'll say A is 71 degrees. And we'll say B is going to be 7 meters. Let me copy this real quick. And let me come down here. And let me paste this in here. Okay. So you remember that formula where we said the area. So the area is equal to 1/2 times, you'll say, in this particular case, I have B and C, so BC. And then times the sine of the angle that's included, so 71 degrees. So what is B, what is C? One is 7 meters and one is 5 meters. So let's just throw this in here. So 7 meters and then 5 meters. And I can't fit this in here, so let me drag this down a little bit. So 7 meters and then 5. Let me slide this down right there so I can make that fit, meters. So basically you'd have what? You'd have 35 meters squared over 2. Let me write that like that. So 35 meters squared over 2 times the sine of 71 degrees. Let's punch that into a calculator. I'll say it's about 16.5 meters squared. So let's say the area. So the area is about 16.5 meters squared. Okay, so we already know how to do it that way. The way I'm about to show you is going to be much slower, but we're going to get a lot of practice. The first thing is I would want to find this missing side lowercase a. Okay, so how do I do that? So a squared is equal to, what's not involved here? You have b squared, and then plus your c squared, and then minus your 2 times b times c, and then times your cosine of the a, okay? So let's go ahead and say a is equal to the square root of all this stuff. So b squared is what? It's 7. Forget about the units. We'll say it's 7 squared plus c squared is 5 squared minus 2 times, you're going to have 5 times 7, okay? And then let me make that a little bit better because my handwriting is getting pretty sloppy. And then times the cosine of this 71 degrees. So let's punch this into a calculator. So I get about 7.2, okay? But how you round here is really going to matter because you're going to end up rounding twice. So I'm going to put 7.2, but that's going to really throw the answer off. So let me put A is about 7.2 meters, okay? So let's get rid of all this. And then let's quickly use our Heron's formula. So we would say, first and foremost, that S is equal to, we would sum the sides. So you'd have 5 plus 7 plus 7.2, which is 19.2, divided by 2 is 9.6. And this is going to be in terms of meters, so you can write that. And then basically with your area formula, so your area, it's going to be equal to, again, the square root of, you take this guy right here. Again, forget the units. So we're going to put 9.6 times, you would do 9.6 minus, in this case, 7.2, which is 2.4. And then you'd have times, you do 9.6 minus your 7, which is going to be 2.6. And then you would do 9.6 minus your 5, which would be 4.6. Punch this into the calculator, and you'll get your area is approximately, I would say about 16.6 meters squared here. So you can see there is a difference based on the rounding. Okay, here with the better formula, we got 16.5 meters squared. Here, because we ended up rounding twice, we got 16.6 meters squared. So again, if you get side angle side, you want to use that first formula. I'm just showing you can do it this way if you get this on a test. Sometimes they want you to do that just to get some extra practice. In this lesson, we want to give an introduction to vectors. And specifically here, we'll focus on finding the magnitude and also the direction angle. All right, so when we work with vectors, we're basically going to see this as a directed line segment, okay? So this is going to have what we call a magnitude or a length, and then also a direction, which is given by the arrowhead, okay? So if I look at this directed line segment with an initial point of O and a terminal point of P, you can see that it has a magnitude or a length, okay? And it also has a direction given by, again, the arrowhead. Now, the way you would notate this would vary by textbook, but I would take my initial point here of O, okay? And I would list that first. That tells me it's the initial point. Then I would take my terminal point P, and I would list that second, okay? That tells me that's the terminal point. So the order here when you're using two letters is going to matter, okay? And then I want to put a little arrow on top, okay? So this is the typical way that you will see this notated. Now, you could also use a lowercase letter, okay, something like, let's say V, okay, something like that, and do the same thing, right? But this one is going to give you the information about, hey, O is the initial point and P is the terminal point. This guy just tells you have a vector, okay? Now, let's erase this for a moment. I want to show you a few other ways that you might see this notated. So in your book, you might see this, okay, where they just put that guy like that, okay? You also might see this listed with a bar on top. And then lastly, you might see them just use a boldface font, okay? So you might see them just do that. Now, I'm going to stick with this for this tutorial. In a few minutes, I'm going to start talking about the magnitude or the length of this guy, okay? And the notation for that is basically where we're going to use these vertical bars. So the magnitude of this vector OP, I could put it in vertical bars to show that. Or sometimes the textbook will use two vertical bars, okay? So go with whatever your textbook goes with. I'm going to use single bars here because that's what my textbook uses. Now, if we look at these two directed line segments or these two vectors, the first thing is if I'm using the two capital letters to name them, this guy would be named OP, okay, that vector OP. Here is going to be your initial point, and here's going to be your terminal point, right? So this guy would be the vector OP, like this. Now, this guy is not going to be the vector OP, okay, because the initial point is here now, and the terminal point is here, right? These have different directions. Look at the way the arrowheads are facing, okay? This one is facing this way, this one is facing this way, okay? So different direction, same magnitude, but this one's going to be called PO, so this will be vector PO, okay? Let me get rid of this and make that a little bit better. Now, I can say right here that this vector OP is not equal to this vector PO. And the reason they're not equal is because for two vectors to be equal, they have to have the same magnitude or the same length, and also they have to have the same direction. These do not have the same direction, even though they do have the same length. So I can say this vector OP is not equal to this vector PO. All right, so now let's think a little bit about the magnitude and how we find that. Also something called the direction angle, and then the component form, okay? So let me start with the component form, because I think everything kind of builds off that. So first and foremost, you see on this sketch, the way this is drawn, we have our initial point at 0, 0, or the origin. Okay, so let me label this. This is 0, 0. Then we have our terminal point at this A, B. Okay, so because this guy has an initial point at 0, 0, we call this a position vector, okay, or we say it's in standard position. Now, when you have a position vector or when it's in standard position, you can just list the coordinates for the terminal point. That's all you need because you know the initial point is at the origin. Okay, you don't need any more information. So the way we list this is called component form. Okay, so here I've named my vector u. So the vector u is equal to, you'll see we have these angle brackets here, and we're just listing the a and the b. All this is the x and the y, okay, from the ordered pair. We're just listing it inside of those angle brackets. So if I said that I had a vector u, okay, is equal to, let's say I had 3, 4, well, I know, and I didn't make those brackets very well, I know that the x location is 3 and the y location is 4 in terms of the point, okay, the terminal point for that vector. So I would start with the initial point at 0, 0, and then I would draw a terminal point at 3, 4, okay, and I would just draw a directed line segment. That's all I'm doing, okay? So additionally, we also have something called, let me just erase all this. We don't need this anymore. We also have something called the magnitude of the vector, which we already talked about. It's the length of this guy, right? So if I said, what is the length of this guy right here? So if I just drew this line right here, what is the length of that? Well, again, normally, if we form a right triangle, okay, we can do this with the distance formula. Let me just call this side C for a moment. So I'll say C, which is the hypotenuse typically, okay? So C, I'll say C squared is equal to this A squared plus B squared. So we know if we want C by itself, we say C is equal to the principal square root, we don't need the negative one, of A squared plus B squared, okay? Well, now instead of C, I just have the magnitude of U, so I'm just going to replace that, okay? That's all I'm doing. So the magnitude of U is just equal to the square root of A squared plus B squared. Now, in the case where you're not given a position vector, okay, you're going to either have to put it into component form or use your original distance formula, right? Remember, the distance is equal to, you have the square root of, you have the quantity x sub 2 minus x sub 1 squared, plus the quantity y sub 2 minus y sub 1 squared, okay? In this particular case, your point down here is 0, 0. So if you do this, it just becomes A, this is going to be A, right, for the x location, A minus 0, which is A, being squared, then plus, this would be B minus 0, okay? So it would be B just being squared, okay? So that's all it is. So let's get rid of this, and we see how to find the magnitude. Now let's talk about how to find the direction angle, because this one's quite confusing, okay? So basically, the direction angle is going to be this positive angle theta here between the x-axis, okay, and our position vector. Now, it turns out that it's pretty easy to find this overall, okay? All you really need to do is some basic trigonometry. In these problems, if you're given A and you're given B, so if you're given this and you're given this, and you're trying to find this angle here, what can you do? Well, remember the tangent is y over x, okay? In this case, it would be b over a. So the tangent, okay, of this angle theta is going to be equal to b over a, and you could say specifically where a does not equal 0, okay? But you're going to have to do more work than this because, again, if you involve the inverse tangent function, remember that guy is going to only return something from quadrants 1 or 4. Okay, so you have to basically think about this by getting a reference angle in most cases and then figure out what quadrant you're in. So you're going to have to do a bit of detective work. Okay, let's go ahead and take a look at a simple problem. So I'm given a vector P, okay, and the component form gives me a horizontal component of -2 and a vertical component of -5, okay? So if you wanted to sketch this guy, you would have one point at the origin, okay, at 0, 0, okay, that's your initial point. And then you'd have a terminal point at -2, -5. Let's just look at the graph real quick. So you see your initial point is here at 0, 0, okay? And your terminal point, you're going 2 units to the left and 5 units down, so it's at -2, -5, okay? It's just a directed line segment. That's all it is. So if we think about the magnitude of this guy, again, that's pretty simple. The magnitude of this vector P is going to be equal to the square root of, again, you're going to square each one and then sum the results. So I'd have -2 squared, okay, make sure you put in parentheses, then plus you'd have -5 squared, okay? So you want the negative and the 5 being squared and the negative and the 2 being squared. Make sure you use parentheses. Okay, so what I'm going to do here is I'm going to say that the magnitude of this vector P is going to be equal to the square root of, let's go ahead and say -2 squared is 4, okay? Plus, if you do -5 squared, that's 25, so that would be 4 plus 25 or 29. Okay, so this is the magnitude of this vector P, okay? Nothing more than just the distance formula. Now, if we think about the direction angle, this is where things get a little bit more tricky. Let me get this out of the way, okay? If I go back, I want you to observe a few things, and I can just erase this. We're trying to find this angle theta here, okay? If we think about this, if we swing this around, we see that this guy is in quadrant 3, okay? So in quadrant 3, if we think about tangent, it's going to be positive, right? Remember this, all students take calculus, okay? But if I use my inverse tangent function, I'm not going to get something in quadrant 3. I'm going to get something in quadrant 1. So if I go back and I think about this guy, remember the tangent of theta is equal to, you take your y value or your vertical component, which is -5, over, you take your x value or your horizontal component, which is -2. And so basically I could say the tangent of theta is really equal to 5/2, right? So if you do the inverse tangent on this, so you do tangent inverse of this 5/2, you're going to get something, let's say it's approximately, I'll go with 68.2 degrees. Okay, so 68.2 degrees. And again, I'm just rounding. So if I know that this guy right here is the result of the inverse tangent function, well, again, if I'm in quadrant 3, this is not my angle. Okay, so people mess up all the time and say, okay, well, theta is going to be 68.2 degrees. That's wrong, because I'm in quadrant 3. So if I go back, you can visualize what's going to have to happen here, okay? I've got to go 180 degrees first, okay? And then I also need to add on top of that, that reference angle to get the rest of the way, okay? So I need 180 degrees plus the reference angle to get this angle here, theta. So if I go back, all I want to do is say theta is going to be equal to 180 degrees plus 68.2 degrees. And you can put approximately here. Let's just leave the equals for a moment. I'll just go ahead and change it in the end. So this is going to be what? It's going to be 248.2 degrees, okay? So let me erase this. We don't need this anymore. So that's our direction angle. It can be a little bit confusing. Just make sure you understand what quadrant you're going to be in, and that when you're working with the inverse tangent function, you're getting something in quadrant 1 or 4 only, okay? So let's go ahead and put this as 248.2 degrees, okay? Also, I should note that if you get something in quadrant 4 from the inverse tangent function, remember, it rotates clockwise to get that, okay? So that's not going to be your angle either, okay? So you got to do a lot of detective work when you're doing these. Okay, so we found that the magnitude of our vector p is the square root of 29, and the direction angle is approximately 248.2 degrees. All right, let's look at another easy one, and then I'll show you something that's a little bit harder. So we have this vector v here, okay, and the horizontal component is -7, the vertical component is -6. So again, if I wanted to find the magnitude, so the magnitude of this vector v, this is equal to the square root of, you could say -7 squared plus -6 squared, okay, like this. So the magnitude of this vector v is equal to, let's go ahead and say this is 49 plus 36, so that's going to be 85 in here. So basically the square root of 85, really can't do anything to simplify that, so that's just going to be our answer, okay? Let's get rid of this, and let's just drag this up here. And again, finding the direction angle usually takes a little bit longer because you got to plug some stuff in. Now, if I think about this again, the tangent of theta is equal to, again, it's going to be the vertical component, -6, over the horizontal component, -7. Might as well just say this is 6/7. But again, if I do the tangent inverse of this guy right here, I'm going to end up with something in quadrant 1. Where is this guy at? If I graph it, again, my initial point is here at 0, 0. My terminal point, I go 7 units to the left and 6 units down. So it's at -7, -6, okay? So if I look at this guy, I'm going to be in quadrant 3, right? This is the angle theta that I'm trying to find. So I've got to swing all the way around here. So remember what we have to do. We've got to go 180 degrees and then plus that reference angle to get there. So let's go back and let's punch this into the calculator. And that's going to give us about 40.6 degrees, okay? So again, when you think about this, I'm going to say that my direction angle theta, I'll just put approximately here. I'll go 180 degrees, plus I'll go 40.6 degrees, okay? So what is this going to give me? It's going to give me 220.6 degrees. So let me erase all of this. Let's just put our answer here. So 220.6 degrees. So again, the magnitude of this vector v is square root of 85. The direction angle is approximately 220.6 degrees. All right, let's take a look at another example. So this one involves a little bit more work. So we have this vector PQ, okay? So we know because of the way this is listed, right, from the beginning of the lesson, we said that the first letter here, P, is the initial point, right? So the coordinates are 2, -9. The second letter, Q, is the terminal point, so the coordinates 1, -4, okay? Let's go ahead and sketch this real quick. So if we look at this guy, we go 2 units to the right and 9 units down, so that's right here. This is going to be your P, or your initial point. Again, this is 2, -9. And then the other one here, if we go 1 unit to the right and 4 units down, we're going to be right there. So that's going to be Q, okay? That's our terminal point. So again, this is 1, -4. So the first thing you want to do if you have a problem like this, you want to put it in the component form. Again, this is where the coordinates for the terminal point are given only because the initial point is at 0, 0, or the origin, okay? So you'll see that I already have this graphed, right? So this is 0, 0, or the initial point. And then you'll see the terminal point is at -1, 5. So where does this come from? How did I get that? Well, if you go back here, it's a simple little formula. All you really want to do, let me come over here, and say for this vector PQ, okay, and sometimes books will rename this with a lowercase letter once it's in component form. That's up to you if you want to do that, okay? I'm going to keep it as it is. So I'm going to say this is equal to, I'm going to put my little angle brackets there. And basically to get this position here, you go with the x value from your terminal point, okay? So I'm going to take this 1 right here, okay? And then I'm going to subtract away the x value from your initial point, so minus 2, okay? So 1 minus 2 gives us negative 1. Now, you want to go in that order. I know sometimes when you work with these formulas, if you reverse them, they come out fine. But in this case, you want to go from the terminal point, okay? You want to start with that and then subtract away from the initial point, okay? So the same thing with x's and y's. So with this guy, I'm going to take this one minus this one, okay? This is from the terminal. This is from the initial. So I want to go negative 4 minus a negative 9, which is negative 4 plus 9, which equals 5. Okay, so that's where that terminal point of negative 1 comma 5 came from. If you go back, you see this is 1 unit to the left and 5 units up. So this is negative 1 comma 5. And you can call this the point Q. Okay, now the point P is at the origin. Okay, and because of this, a lot of books, again, will just rename this as the vector V or U or whatever they want to do. I'm just going to keep it like this. Now, if you want to find the magnitude, okay, and make another little border here, of this vector PQ, okay, what I'm going to do is just take the square root of, I'll take this first guy, negative 1 squared, plus the second guy, 5 being squared. Okay, so the magnitude of PQ, okay, like this, is going to be the square root of negative 1 squared is 1, plus 5 squared is 25, so that's going to be 26. So it's just the square root of 26. Now, if you wanted to come over here and use these points, again, you could plug into the traditional distance formula. You could say, and I'm just going to label this as the magnitude of this PQ guy. Okay, I'll show you it's the same. Basically, you're going to subtract this guy minus this guy. So x sub 2 minus x sub 1. So it's going to be 1 minus 2. Let me write this out. So 1 minus 2, this is squared. Then plus, you're going to do this guy, that minus this guy. So negative 4 minus a negative 9 is plus 9. Okay, this is going to be squared. And we want the square root of this guy. Okay, so notice that we already did this to find these guys right here. Okay, so we're a step ahead. Right, so that's why we do this first, and then we don't have to do all this, okay? So 1 minus 2 is going to be negative 1, so it's negative 1 squared, which you know is 1. And then negative 4 plus 9 is 5. 5 squared is 25. So this becomes square root of 26, okay? Just like it is over here. Okay, so you see it's the same magnitude in each case. Now, let's talk a little bit about the direction angle. So theta, this is what? Well, again, let me actually erase this. Let me just say that the inverse tangent, I think we can kind of skip ahead a bit. The inverse tangent of what? Well, I'm going to take the vertical component, which is 5, over the horizontal component, which is negative 1, which really I could just write as negative 5, okay, like this. Now, when you talk about putting a negative as the argument for this inverse tangent function, you're going to get something in quadrant 4, okay? So in this particular case, if we think about this, this horizontal component is negative, this vertical component is positive. If I think about it, where am I going to be? I'm going to the left and I'm going up. So I'm going to be in quadrant 2. If you want to see this graphed on its own, you'll see, again, my terminal point here is that we go 1 unit to the left and we go 5 units up. And you see I'm in quadrant 2 here, okay? So basically, when I do my inverse tangent function, I'm going to end up with something in quadrant 4, and also I'm going to be rotating clockwise, okay? So I want to just take the absolute value of that and think about that as my reference angle. And then what I want to do, in this particular case, I would think about the fact that, okay, if I had an angle of 180 degrees, I want to subtract off and go back by the amount of the reference angle, right? So I want 180 degrees minus the reference angle to get this angle theta here, okay, this angle theta here. Now, let's go back. So I'm going to get about negative 78 point, let's say 69. So let me kind of slide this down because I don't think it's going to fit. So I'll put it's approximately negative 78.69 degrees. Now again, what I want to do is I want to think about this in terms of absolute value. So in quadrant 2, I want an angle with a reference angle of 78.69 degrees. So all I'm going to do, get rid of the negative sign, I'm going to say theta is approximately 180 degrees minus this 78.69 degrees. And that's going to be about 101.31 degrees. So let's just erase this and put it's about, or approximately, 101.31 degrees. All right, for the last two examples, we're basically going to reverse things. So now we're going to be given the magnitude of a given vector, and we're also going to be given the direction angle, and we have to come up with the component form, okay? So let's think a little bit about this angle theta, and let's think about if I had this guy B and I had this guy A, well, let's think about some relationships here. I know that the sine of this angle theta is opposite, okay, over the hypotenuse, which in this case would be the magnitude of this vector u, okay? So I can say that the sine of this angle theta is equal to, we'll go ahead and say this b here, which is the vertical component, over the magnitude of this vector u, okay? So I'm going to be given the angle theta, and I'm going to be given the magnitude of this vector u, so I should be able to plug in there and figure out what b is, okay? Then also if I think about the cosine, so the cosine of theta, what is that? Well, that's now adjacent, so let me erase this. That's the adjacent over the hypotenuse. So this would be a over the magnitude of this u guy, okay? So we can use these two. We'll just basically solve them for a and b, okay? And then we'll plug in and we'll have our answers. So let me just paste this in here and let me drag this over a little bit. We can solve this for a and b to come up with a nice little formula to use here. So basically, if I multiply both sides here by the magnitude of this vector u, you're going to see that b is equal to, you would have the magnitude of this vector u and then times the sine of this direction angle theta, okay? Then here, a is equal to the magnitude of this vector u times the cosine of theta, okay? Let's get rid of this. Now we have a little formula to use. So I'm given the magnitude of some vector n, okay? So I want to find the component form. And basically, all I'm going to do is think about this and this. So I want the a and the b. So the a goes here, the b goes here, okay? That's all we're doing. So the first one for the a, you're going to think about going down here. The magnitude, in this case, of our vector n is 27. So I'm going to have 27, let's put a equals this, so 27 times the cosine of the direction angle, theta, in this case is 300 degrees. Now first off, a 300 degree angle is in quadrant 4. Cosine is positive in quadrants 1 and 4, okay? So we know that this guy's going to be positive. Now 300 degrees has a reference angle of 60 degrees, and cosine of 60 degrees is going to be a half. So I can just put times a half here, and this is basically 27 over 2. Okay, so 27 over 2. Okay, and then for b, it's equal to what? So in this case, again, the magnitude of this vector n is 27, and times the sine of this guy, 300 degrees. So again, think about the fact that in quadrant 4, your sine is going to be negative, right? Sine is positive in quadrants 1 and 2 only. So in quadrant 4, it's going to be negative, okay? So I'm going to put negative, and then the reference angle is 60 degrees. So sine of 60 degrees is square root of 3 over 2, okay? So all this is, you're not going to be able to really simplify this too much. You're going to say this is negative, let me put this out in front. So the negative of 27 times the square root of 3 over 2. Let me close my brackets down. So this would be your component form for this vector n. Let's look at one more of these. So again, all I'm going to do here, let's go ahead and write this vector k like this, is equal to, I'm going to set up my brackets, and again, this is a comma b. So a is equal to, again, with the horizontal, you're thinking about cosine, right? So all it is this guy right here times the cosine of this right here. So 32 times the cosine of 120 degrees. Now this again has a 60 degree reference angle, but now I'm in quadrant 2 and cosine is negative in quadrant 2. So this is going to be negative half, right? So negative 1/2. So this will end up being negative 16, right? So if we put this in here as negative 16, because this will cancel with this and give you 16, okay? And obviously this is times negative 1, so that's where the negative comes from. Okay, let's get rid of this. Let's think about b now. So b is equal to, you're going to take the same 32, the magnitude of this vector k, times now the sine, okay, the sine of this 120 degrees. Well, I'm in quadrant 2, okay, I have that same 60 degree reference angle, but now sine is positive, okay? So this is going to be times square root of 3 over 2. And so this is going to cancel with this and give me 16. So this is 16 times the square root of 3, okay? So 16 times the square root of 3. So that's going to be our component form, and maybe I should make that 3 a little bit better, okay? For this vector k, again, your horizontal component is negative 16. Your vertical component is 16 times the square root of 3. In this lesson, we want to continue to talk about vectors, and here specifically, we're going to focus on operations with vectors. All right, so let's start out here by talking about how to add two vectors together. So the sum of two or more vectors is also a vector. This is referred to as the resultant vector, or some people will just call this the resultant, okay? So basically, let's say I had this simple example here, very generic, and on the left, I have this vector with a horizontal component of A and a vertical component of B. And I want to add this to this vector on the right, where there's a horizontal component of C and a vertical component of D. So for my resultant vector, or just the resultant if you want to say that, basically I'm going to do A plus C, so A plus C, okay, then I'll do a comma, and then I'm going to do B plus D, so B plus D, okay? That's all it is. It's very, very simple. You're going to sum these horizontal components, so A plus C, that's going to give me the horizontal component for my resultant vector. Then I'm going to sum these vertical components, so B plus D, that's going to give me my vertical component for my resultant vector. And you can do this with more than two. Let's say, for example, I had something like 2 and then 3 here, okay? And then let's say plus, we'll do maybe 4 and then 5 here. And let's say we do plus, let's say we do 6, and then you could even do like negative, so negative 9. Okay, so something like this. So all we would do, if we wanted to find the sum here, you would say that you would have 2 plus 4 plus 6. So 2 plus 4 is 6, 6 plus 6 is 12. Okay, so that's the horizontal component for this resultant vector. And then for the vertical component, you're going to do 3 plus 5 plus negative 9. So 3 plus 5 is 8. 8 plus negative 9 is going to be negative 1. Okay, so this resultant vector, the horizontal component is 12, and the vertical component is negative 1. All right, let's also talk about how to show this geometrically. We can do this with a triangle, and we can also do it with a parallelogram. So using the triangle method, let's think about this. We have this vector A and this vector B. They're being added together. So let's say I started by just sketching vector A. So this is the initial point, and this is the terminal point. So I've just sketched vector A. Then for vector B, I'm going to use my horizontal and vertical components to sketch this guy. Again, the initial point's here. Your terminal point would be here, let's say, okay? And then your resultant vector, or basically the vector A plus the vector B, is going to be this guy right here. So this vector right here. So you'll notice that the initial point for this vector is going to be the same as the initial point from the vector A. Then the terminal point from this vector is going to be the same as the terminal point from this vector B. Okay, so that's all you're doing. So for this example, let's go ahead and say we have the vector t, okay? We're going to add to this our vector u, So what is this going to give us? So for the vector t, you have a horizontal component of 6 and a vertical component of negative 8. For the vector u, you have a horizontal component of 3 and a vertical component of 4. So in this resultant vector here, to get the horizontal component, I'm going to take this 6 and add it to this 3, right? So just sum the horizontal components. So 6 plus 3 is 9, okay? For the vertical component, I'm basically going to sum the vertical components here. So negative 8 plus 4 is going to be negative 4, okay? So this guy basically would have an initial point at the origin, okay? It would have a terminal point at 9, negative 4. So let's look at this graphically. Let's start out by just redefining things. So we had this vector t, okay? In component form, this was 6, negative 8. So we had a horizontal component of 6, a vertical component of negative 8. Then for the vector u, we had a horizontal component of 3 and a vertical component of 4. Then for this resultant vector, so the vector t plus the vector u, we basically what? We said 6 plus 3 was 9, and we said negative 8 plus 4 is negative 4, right? So a horizontal component of 9 and a vertical component of negative 4. Okay, so looking at the graph here, you see for vector t, we started with an initial point here at the origin, right? It's just in standard position. So the terminal point is going to be right here, which is at 6, negative 8, okay? So we went 6 units to the right, and we went 8 units down. So that's as expected. This vector u, when you try to sketch that now, the initial point has to be at 6, negative 8. So you're using the 3 as the horizontal movement, right? So I'm just going 3 units to the right. And then I'm using the 4 as a vertical movement. So now I'm going 4 units up. So 1, 2, 3 units to the right. That puts me at 9 on the x-axis. And then 4 units up, 1, 2, 3, 4. That puts me at negative 4 on the y-axis. So this point right here would be 9, negative 4, okay? And this is consistent with what we said, right? So basically, this vector right here, this resultant vector, has the same initial point, okay, as this vector t, and has the same terminal point as this vector u. All right, now let's think a little bit about this parallelogram method. This one's a little bit harder to draw, especially if you're not working on a coordinate plane. But essentially what you want to do here is have the initial point for the vector A and for the vector B to be the same, okay? So everything's going to have the same initial point. Then you'd have your normal terminal point, your normal terminal point. So these are easy to draw, especially if you're on the coordinate plane. The next part is a little bit more challenging. You're going to complete a parallelogram. Essentially what you're going to do is you're going to take this side right here and just slide it down, okay? So you would have it like that, okay? And then basically this point right here is going to help you set up this diagonal. So this is going to be your resultant vector, okay? Now you could also do it this way, okay, where you take this side right here and basically copy it and slide it down. And if you want to form the full parallelogram, you need to do that, right? So basically with the parallelogram, okay, in case you're unfamiliar with this, you're going to have opposite sides that are going to be equal in length, and they're also going to be parallel, right? So this side and this side right here are the same length and they're parallel. And then this side and this side are the same length and they're also parallel. Now, let's take a look at this with an example. We have this vector t, which is a horizontal component of -1 and a vertical component of 8. We have this vector u, which is a horizontal component of 4 and a vertical component of -3. So if I did the vector t plus the vector u, again, all I need to do is, for this guy right here, for the horizontal component, I'm going to do -1 plus 4. So that's just going to give me 3, okay? For the vertical component, I'm going to do 8 plus -3, which is going to give me 5, okay? So all I want to do is sketch this. All right, so let's write this out again. So the vector t is going to be with a horizontal component of -1 and a vertical component of 8. Then the vector u is going to have a horizontal component of 4 and a vertical component of -3. So the resultant vector, when you do this vector t plus this vector u, this is going to be -1 plus 4, which is 3, and then 8 plus -3, which is 5, okay? So you can see this graphically. It's a little bit more busy than the triangle drawing, but it's still there. So if you look at the first guy, so the vector t, here's the initial point at the origin, and then the terminal point right here is going to be at -1, 8. So 1 unit to the left, 8 units up. So this is -1, 8. Then if you look at your vector u, okay, your initial point is also at the origin. The terminal point here, okay, would be at this point 4, -3. Okay, so 4 units to the right, 3 units down. And then basically if you wanted to draw this, you already know the terminal point of this resultant vector is here, okay, which is at 3, 5. And you could basically sketch this guy right here, okay, and this guy right here. Those sides there, again, this side right here, okay, is going to be the same length and parallel to this side right here. Then the other one's the same thing. So this side right here and this side right here, same length, and then are also parallel, okay? So when you look at this guy, you would then draw this vector here, okay, where basically the initial point is the same as the other two vectors, and your terminal point is right there, okay? So it's going to be at that 3, 5. Okay, let's talk about this multiplying a vector by a scalar. Also very easy. So let's say you had some real number k, and it was multiplied by this vector with a horizontal component of a and a vertical component of b. Well, the result of this is going to be a vector with a horizontal component of k times a and a vertical component of k times b, okay? So the reason they call it a scalar is you can think about this as scaling your vector, okay? So graphically, you can think about it like this. Let's say we had some vector u, okay, so this is u to start. If you had half times this vector u, we can see that it's half as long, okay? If you had 2 times this vector u, now it's twice as long, okay, compared to this original vector u. Now, when you get a negative involved, what it's going to do is it's going to give you an opposite direction, okay? So basically, if I had the negative of this vector u, it's going to flip the direction, right? So it's the same length, but the direction is flipped, right? It's the opposite direction. Then if I had -3/2 times this vector u, well, now it's the opposite direction, and basically compared to this original vector u, in terms of its length, it's going to have 1/2 of the vector u added on, right? So it's like I took this vector right here and added this vector right here onto it, and then I gave it the opposite direction to form this vector here, which is -3/2 times the vector u. Okay, let's find the -2 times the vector v, and then I'll show you this graphically. So we have the vector v, horizontal component is -3, vertical component is 4. So if I wanted -2 times this vector v, then all I would do is -3 times -2, which is +6. And then I would do -2 times 4, which is -8, okay? So this guy right here, this -2 times this vector v, is going to be 6 for the horizontal component and -8 for the vertical component. Now graphically, the original vector v, again, when we look at this, is going to have a horizontal component of -3 and a vertical component of 4. Okay, so you see it starts at the origin, that's the initial point. And then the terminal point is right here, again at -3, 4. Okay, so 3 units to the left, 4 units up. Now, if I look at -2 multiplied by that vector v, so -2 multiplied by this vector v, again, I'm scaling this because this guy is twice as long, okay, that's the 2 part, and then it's going in the opposite direction, that's the negative part, okay? So basically, I'm multiplying everything here by -2, so this is 6, and this is -8, and you'll see that the initial point is the same, the terminal point is here, I went 6 units to the right, 8 units down, this is 6, -8. Okay, so you can see this guy right here is twice as long, and it's also going in the opposite direction. Okay, so let's combine these two concepts together. So now we have this vector v, horizontal component of -2, vertical component of 5. And then we have this vector w with a horizontal component of 3 and a vertical component of 4. We want to find -3 times the vector v plus 2 times the vector w. Okay, so all I'm going to do is set this up and say -3 times this vector v plus 2 times this vector w is equal to, I'm just going to put a -3 out in front of this, so -2 and then 5 is inside, and then plus, I'm just going to put a 2 out in front, and then I'm going to put a 3 and then a 4 inside. Okay, so that's all I'm doing. So what I'm going to do is just first multiply. So let me copy this down, or I could just put equals to keep this going. I'll say basically each part of this is going to get multiplied by -3. So this would be -3 times -2, which is 6, and then -3 times 5 would be -15, okay? Then plus 2 times 3 is 6, and then 2 times 4 is going to be 8, okay? So now I just want to find the sum. Again, very, very easy. I'm going to add the horizontal components, so 6 plus 6 is 12. Then I'm going to add the vertical components, so -15 plus 8 is -7, okay? So in the end, this -3 times this vector v plus this 2 times this vector w gives me this vector, okay, with a horizontal component of 12 and a vertical component of -7. All right, let's wrap up the lesson and look at something that involves a concept from the last lesson. So we have the magnitude of this vector f is 17. The direction angle theta is 212 degrees. The magnitude of this vector b is 22, and the direction angle theta is 10 degrees. So what if I wanted to find the vector f minus the vector b? What would I do? Well, first I need to find the horizontal and vertical components for each. So remember how to do this. For the vector f, to set this up, I would do what? I would take my magnitude, 17, and for the horizontal component, I'm multiplying by the cosine of this direction angle, which is 212 degrees. And then for the other one, it's going to be 17 times the sine of 212 degrees. Okay, that's all I'm doing. Then for b, this vector b, what I would do is I would do 22 now, the magnitude of this guy, times the cosine of, in this case, 10 degrees, okay? And then I would do 22 times the sine of this 10 degrees as well, okay? So you can punch that up and get approximations and then set up your subtraction. Or if you want to, you can go ahead and do this all in one step. So we could basically say 17 times the cosine of 212 degrees minus 22 times the cosine of 10 degrees, okay? Then comma, you would have 17 times the sine of 212 degrees minus 22 times the sine of 10 degrees. Up to you, how do you want to do it? You get the same answer either way. Actually, the rounding might be a little bit different, but let's just go ahead and do it the long way. Just get some practice. So first, I'm just going to say the vector f is going to be, and let me put approximately here, because I'm going to approximate this. 17 times the cosine of 212 degrees, I'll say that's about negative 14 point, let's just go ahead and say 42, okay? This guy, 17 times sine of 212 degrees, is going to be about negative 9.01, okay? So this is my vector f, and again, this is an approximation. So let's scroll down and get a little bit more room so we can stay on the screen. I'll do my vector b now, so this is approximately. We'll go ahead and set this up and say 22 times cosine of 10 degrees. It's going to be about 21.67, so 21.67. And then 22 times the sine of 10 degrees is going to be about 3.82, okay? So now, let me make this a little bit better. And let me change these. I'll make them a little bit better. A little bit better, okay. So now if I come down here, if I want to do the vector f minus the vector b, all this is going to be is negative 14.42 minus 21.67, comma, I'm going to have negative 9.01 minus 3.82, okay? And I put equals. It should probably be approximately to be more precise. So let me go ahead and put that like that, okay, to make that better. And let's just go ahead and correct this out. So I'll say this is approximately, and I'll put my little symbol there, say about negative 36.09, right, for negative 14.42 minus 21.67. Then over here, negative 9.01 minus 3.82. We'll say this is negative 12.83. Again, this is an approximation, okay? So the vector f minus the vector b, the horizontal component would be about negative 36.09, and the vertical component would be about negative 12.83. In this lesson, we want to continue to talk about vectors, and here specifically, we're going to focus on unit vectors, the dot product, and then the angle between two vectors. All right, so to start the lesson, we're going to talk about something called a unit vector. So a unit vector is just a vector that has a magnitude of 1, okay? So let's say that we denote our unit vector with a u, okay? When you work with a unit vector, you're going to have a special notation. Some people call this a cap, some people call it a hat, but basically this tells you have a unit vector, okay? And if you have a unit vector, the magnitude of this unit vector, again, let's call it u, is always going to be equal to 1. So for some problems, you're going to be asked to find a unit vector, let's call it u, that has the same direction as a given non-zero vector, let's call it v. And basically, to solve this type of problem, you're just going to take your vector v and divide it by the magnitude of that vector v, okay? And that's going to give you your unit vector u. Now, if you're confused by me saying it, it's okay. The formula is very, very simple. So basically, this unit vector u is equal to the vector v, okay? So the vector v divided by the magnitude of that vector v, okay? So you can really think about this as multiplying by a scalar, 1 over whatever this is. So I'll further break this down and say this is the vector v times 1 over whatever this result is, so the magnitude of this vector v. Remember, in the end, this is going to be a number, right? This is some number, okay? So if I wanted to practice on this one, let's say this vector v, okay, has a horizontal component of negative 5 and a vertical component of negative 12. How would I find the unit vector u in the direction of v? So basically, in the direction of v, but now I have a magnitude of 1. So what I would do is I would first find the magnitude of v. So the magnitude of v, hopefully you remember that formula. You're going to take the square root of, I'll have negative 5 being squared, plus negative 12 being squared. So each one of these guys is going to be squared, and you're going to find the sum of those two results, okay? So I know negative 5 squared is 25, negative 12 squared is 144. So this would be my vector v, the magnitude of that guy, would be the square root of 25 plus 144 is 169, and the square root of 169 is 13, right? So the magnitude of this vector v is going to be 13. Okay, so that's easy enough. Once you have this result, you can basically just divide, okay, divide each one of these components by the magnitude of that vector, and you're done, right? You've set up your unit vector u, okay? But if you want to kind of go about this the long way, let's just go ahead and use this formula here. So you have your vector v. I'm going to write it in component form. So I'm going to say this is negative 5, comma negative 12. And let me make these a little bit wider, okay, so it's more consistent. So like that. And I'm going to multiply it by 1 over the magnitude of that vector v. So 1 over, in this case, it's 13. So you can see this is just a scalar multiple, right? So I can either multiply by 1 over 13, or I can just divide by 13. Doesn't matter, right? So in the end, my unit vector u, okay, would be equal to, in component form, you'd have negative 5 over 13, comma, negative 12 over 13, okay? That's all you need to do. I want to prove a few things to you. One, that the magnitude of this vector u is 1, and also that the direction angle is the same, okay? So for the magnitude, again, it's very, very easy. So the magnitude of this unit vector u is going to be the square root of, so let's go ahead and say this is going to be negative 5 over 13 being squared, plus you're going to have negative 12 over 13 being squared, okay? So negative 5 over 13, if you square that, negative 5 squared is 25, 13 squared is 169. So let me write this down here. The magnitude of this vector u is going to be equal to the square root of, this would be 25 over 169, then plus negative 12 squared is 144, and then 13 squared again is 169, okay? So if you add these guys, you have a common denominator. 25 plus 144 is 169. So you get the square root of 169 over 169. This is obviously 1. and the square root of 1 is 1. So you can see the magnitude of this unit vector u is 1. Okay, so that part works out. Now, what about the direction angle? Okay, you're going to see that basically if you think about the direction angle, remember the tangent of theta is going to be equal to this negative 12, okay, over this negative 5, right? Which in this case, you might as well just say it's 12/5, right? But again, we have to think about what quadrant we're in, because if we do the inverse tangent, okay, we're going to, in this case, because this is positive, we're going to get something in quadrant 1, okay? But this is in quadrant 3 because we have a negative x value and a negative y value. So I go to the left and I go down, so I'm in quadrant 3. So what I want to do here is say the inverse tangent of this 12/5 here would be equal to, or let's say approximately, because we've got to punch this into a calculator, I get about 67.38 degrees, okay? And because we're in quadrant 3, we want to add 180 degrees to this, okay, to get our measurement for theta, okay? So we'll say theta is approximately, I'll say 247.38 degrees, okay? So this is your direction angle. You already know how to find that. Now, if you look at it for this unit vector u, you'll notice you're still in quadrant 3, right? This is negative and this is negative, okay? So you're still in quadrant 3, and I want you to think about the fact that you'd still have tangent of theta is equal to, now it would be negative 12 over 13 divided by negative 5 over 13. Well, the negatives are going to cancel, right? So you'd have 12 over 13 times, flip this guy, 13 over 5, okay? And the 13s are going to cancel, so I'm back to this 12/5, right? So the tangent of theta is equal to 12/5, and again, I'm still in quadrant 3, so I go through the same steps, and I'm going to end up with a theta here, okay, my direction angle, which is again approximately 247.38 degrees. So you see that we've set up this unit vector u that has a magnitude of 1, and it's in the direction of our vector v. All right, let's change our problem up just a little bit. So sometimes you'll be asked to find a unit vector u basically in the opposite direction of some vector v. So all you really need to do here is think about the concept of, well, if I multiplied a given vector by -1, it's just that vector that has the opposite direction, okay? Same magnitude, but an opposite direction, okay? So we're going to use that concept here and just multiply our regular answer by -1. So in other words, I would have my unit vector u is going to be equal to, we'll have this vector v times, what I'm going to do here is put -1, okay, instead of +1, so -1 over the magnitude of this vector v. So let's go ahead and find the magnitude of our vector v. So the magnitude of this vector v is going to be equal to the square root of, so 4 squared is 16, plus 12 squared is 144. If you add these guys together, you get 160. And what I can do is I can factor this and say this is 16 times 10, okay? 16 is a perfect square. So this would be 4 times the square root of 10, okay? So I'll say this is 4 times the square root of 10. Now, all I'm going to do here is either divide everything by the negative of this guy right here, or you could say multiply by -1 over that guy, whatever you want to do. I'm just going to make this a little bit quicker and say my unit vector u that I'm looking for in this case is going to be, I'll take the 4, okay, and I'm going to divide it by the negative of 4 times the square root of 10, okay? And then let me put my angle brackets in here. And then I'll have my 12, and then I'm going to divide that by the negative of 4 times the square root of 10, okay? If I didn't ask you for the opposite direction, this would be +1, but since I did, it's a -1 there, so that's why these are negative here. Okay, let me get some room going here. So let me go ahead and set this up as the unit vector u is equal to, put my brackets there. So we know we're going to have to rationalize the denominator there. So 4 divided by 4 is 1. So let me put a negative out in front. Let me put a 1 over the square root of 10. And I'll just multiply this by the square root of 10 over the square root of 10 to get that out of the way. So this becomes 10 down here, okay? And up here, this is the square root of 10. Okay, so this is the square root of 10. Now, it is common to not rationalize the denominator for these examples. It's really up to you or your teacher. Just get with them and see what they want you to do. For this one, we have 12 divided by 4, which is 3. And of course, you have the negative. So let me go ahead and put 3 over the square root of 10. And again, I'm going to rationalize the denominator. So times the square root of 10 over the square root of 10. Okay, so we're going to multiply by that. So in the numerator, I'd have 3 times the square root of 10. So 3 times the square root of 10. In the denominator, I would have 10, right? So basically, the way this guy would work is you would have this unit vector u, which again is in the opposite direction of my vector v. The horizontal component is negative square root of 10 over 10, and the vertical component is negative 3 times square root of 10 over 10. All right, so let's continue to talk about these unit vectors. And now you're going to see these two extremely useful unit vectors, which are defined using this I and also this J, okay? So you see on the screen here, we have this little graph. You have a directed line segment that starts at 0, 0, okay, and ends or terminates at the point 1, 0. So the initial point is 0, 0, or the origin. The terminal point is 1, 0. So we have this unit vector I, okay? In component form, this is 1, 0 like this, okay? This is not the imaginary unit I, so please don't get confused by that. Then, similarly, we have this guy that is denoted with a J. So we'll say J here with my little hat. So this guy, it terminates at 0, 1, okay? And basically, we're going to use this guy to rewrite something like this. So our vector V, in component form, we have A, B, okay? But using those two vectors I and J, basically what you can do, again, because the vector I in component form is 1, 0, okay, and the vector J in component form is 0, 1, you can take your horizontal component and multiply it by this guy. So let's say the vector V, I could also define it saying it is this A multiplied by this 1, 0, okay, then plus, and I probably need to move this down a little bit, so plus this B here multiplied by this guy 0, 1, okay? So you know that these are just scalar multiples at this point. If I multiply through, this is basically A, 0, okay, plus this is 0, B, okay? And then if I add these two together, I'm right back to what I started with. So I didn't do anything illegal. Now, what you can do at this point is just replace, in each case, this with the unit vector I and this with the unit vector J, okay? That's all you're going to do. This is called writing it in the I, J form, or you might hear it as a linear combination of the standard unit vectors I and J, okay? So I'm going to say the vector V now is going to be written as A times the unit vector I plus B times the unit vector J, okay? So if you see something in this form, to put it in component form, basically, again, the vector V is what? It's just in component form, this is your horizontal component, right? And then comma, this is your vertical component. That's all it is, okay? If we look at a little example here, let's say I have some vector P, and I want to write it as a linear combination of those two standard unit vectors I and J. All I'm going to do, I'm going to say this guy P, this vector, is -5. This is the horizontal component multiplied by this unit vector I, okay? Then plus this guy 4, okay, multiplied by that unit vector J. That's all it is. Again, if you go back through this the long way, all you're really saying is that this vector P is equal to, you'll have -5 times, this is what, 1, 0, then plus 4 times, this is 0, 1. And again, all I'm doing is, if I kind of move this up here because I'm going to run out of room, this vector P is what? Now it's -5, okay, 0, plus, and let me move this down a little bit so I can fit everything. Let me change this up because I'm getting sloppy with my notation there. So plus, over here, this would be 0, 4. Again, if you add these guys together, this vector P is back to what it started with, right? This is going to be -5 plus 0, which is -5, and then comma 0 plus 4 is 4, okay? So it's just two different ways to write the same thing. This way right here, you're going to see a lot, okay? So you need to know how to go back and forth between the two. If you wanted to graph something like this, the terminal point is going to be at -5, 4. So if we looked at this on our little coordinate plane here, again, the horizontal movement here is given by the -5 times this unit vector I, okay? It's just basically like if I said the horizontal movement here is given by this -5, 0, right? And let me make that a little bit better. So basically if I started here and I went 5 units to the left to end up right there, okay? That's my horizontal movement given by this -5 times the unit vector I. Then for the vertical movement, if I'm starting here and if I go up, well, basically this is given by 4 times the unit vector J, right? 4 times that 0, 1 like this. So this is 0, 4, right? I'm just moving up 4 units vertically. So when you put those two guys together, you end up with this directed line segment with a terminal point at -5, 4. 5 units to the left, 4 units up. So that's all it is. All right, let's talk about something called the dot product now. And this is going to lead us into a topic called finding the angle between two vectors, okay? So we start with the dot product, and the dot product of two vectors is going to be a real number. So this is not going to be a vector. This is also called the inner product, okay? So someone might refer to it that way. Now the dot product for us is going to be used to determine the angle between two vectors, and we'll get to that shortly. So when you have the dot product of two vectors, let's say u and v, so I have u and v, those two vectors. I'm going to write the vector u, then dot the vector v. Okay, so this is the dot product. And basically all I'm going to do is I'm going to multiply the first component here by the first component here. So A times C. So in other words, horizontal component times horizontal component, then plus second component here times second component here. So vertical component here times vertical component here. So B times D. It's a very easy pattern to remember. Once you do a few examples, it just becomes second nature. Okay, so let's look at an example. So we want to find the dot product of this vector u and this vector v. So you're going to do the vector u dot the vector v like this. And again, if this is confusing for you, because again, it's as this linear combination of the unit vectors I and j, you can always put it in component form. So the vector u is, again, in component form. This is my horizontal component. This is my vertical component, okay? Do this a few times, and then it becomes very easy, right? So the vector v, this is my horizontal component. This, and the whole thing with the negative, so let me make sure I do that properly. This is your vertical component, okay? So either way you want to do it, but all I'm going to do here is I'm going to say 7 times 3. So 7 times 3, so first times first, then plus 6 times negative 4, so second times second. So 6 times negative 4. That's all you're doing, okay? Just match things up and say these guys are being multiplied, and then these guys are being multiplied. That's all you got to do. So once you have this set up, 7 times 3 is 21. Then basically plus 6 times negative 4 is negative 24. So this would be negative 3. So that's your dot product of this vector u and this vector v. Okay, let's look at another example. If you want to pause the video and put these in component form, that's up to you. I think you can get it like this. So the vector u is negative 2 times the unit vector I plus 8 times the unit vector j. Then this vector v is 4 times the unit vector I minus 6 times the unit vector j. So the dot product of this vector u and this vector v, so u dot v, would be what? You're going to have this guy times this guy, right? So first times first. Negative 2 times 4, then plus this guy times this guy. So 8 times negative 6. 8 times negative 6. And again, if something's negative, make sure you take that with it, okay? So let's put equals here. Negative 2 times 4 is negative 8. And then plus 8 times negative 6 is negative 48. And of course, this is really easy. This is just going to be negative 56. All right, so now that we understand how to find the dot product of two vectors, we're going to use this now to find the angle between two non-zero vectors. So let's suppose we have these two non-zero vectors, let's call them u and v, okay? And we want to find the angle between them, and we'll call this angle theta. So we'll say that theta is greater than or equal to 0 degrees and also less than or equal to 180 degrees. Or we could say theta is greater than or equal to 0 and less than or equal to pi if you want to work with radians. So we can come up with this little formula here. This is derived from the law of cosines. So we have the cosine of this angle theta is equal to the dot product of this vector u and this vector v over, you have the magnitude of your vector u times the magnitude of your vector v. Okay, so that's all it is. If you want to find theta, you're going to use your inverse cosine function, okay? You're just going to be punching this stuff into a calculator. So really, really easy. All right, let's look at the first example. We have a vector u, okay, which is negative 6 times the unit vector I minus 5 times the unit vector j. Then we have this vector v, which is 4 times the unit vector I plus 8 times the unit vector j. Okay, so if I want to basically set this guy up, first and foremost, if you're still confused by these linear combinations of the unit vectors I and j, you can always write this in component form, okay, to ease your confusion. Again, all I'm going to do that is take this guy as a horizontal component, okay, and then this guy is the vertical component. That's all I'm going to do. So if you're confused at this point, just do that for a little while, and then eventually this will click for you. So then this guy for the vector v, in component form, it's going to be 4, comma, then you're going to have 8. Okay, that's all it is. So if I want my dot product, okay, so the dot product of this vector u and this vector v, this is going to be what? Negative 6 times 4, that's negative 24. Then plus negative 5 times 8, that's going to be negative 40, okay? So this gives me negative 64. Then if I want the magnitude of this vector u, okay, this is going to be the square root of, so I'd have negative 6 squared, that's 36, and then plus negative 5 squared, that's 25. So this would be the square root of 61, okay? Then the magnitude of this vector v, let me change my ink color here. This is going to be the square root of, 4 squared is 16, and then 8 squared is 64. So 16 plus 64 would be the square root of 80. You could simplify that if you wanted to. Again, you're punching this stuff into a calculator, so if you're trying to save time, I wouldn't even worry about it. But since this is a math tutorial, I'm going to take the extra step and write this down here. Let me just put this as a square root of 61. And let me write this, instead of the square root of 80, let me say that 80 is 16 times 5, and 16 is 4 times 4, right? So I'm going to say this is 4 times the square root of 5, right? Because 16 is just a perfect square. Okay, so now we have everything we need. Let me tighten this down, put negative 64 here. Hopefully you have this copied down. I'm going to get rid of it because I need the room. And I'm basically going to write my formula here. So the cosine of theta is equal to, again, the dot product, so of this vector u, so the vector u dot the vector v. And then this is over the magnitude of this vector u, and then this is multiplied by the magnitude of this vector v, okay? So what I would do here is just plug in to the calculator, and essentially you're going to say that theta is equal to the inverse cosine of all this, right? So your dot product of the vectors u and v, so this is going to be negative 64. Then over, you're going to have the product of these two magnitudes. So the magnitude of vector u is square root of 61. And then the magnitude of vector v is 4 times square root of 5. So that would be 4 times the square root of 305. Okay. And again, you don't have to write all this out. If you're using a calculator, just punch it into it and you're done. But you might want to consider the fact that you should put parentheses around this guy when you punch it into your calculator. If you keep getting the wrong answer, that's usually what's going on. It just depends on your calculator, okay? So what I would do is punch this guy into the calculator as the argument for the inverse cosine function, and I'll say theta is approximately 156.37 degrees. Okay, so that's basically all you're going to do. And again, if you keep getting the wrong answer with your calculator, if it says something like domain error or something like that, then make sure you wrap this part right here inside of parentheses, and that should clear that up for you. Okay, let's take a look at another one. We should know the formula at this point. Let me go ahead and do the dot product first. So the dot product of u and v, so u dot v here, is going to be what? 2 times 3, which is 6, plus negative 8 times negative 5, which is going to be 40. So this is 46, okay? And then basically the magnitude of this vector u is the square root of, you have 2 squared, which is 4, then plus, you have negative 8 squared, which is going to be 64. So 4 plus 64 is 68, right? So square root of 68, again, you could simplify that. It's 17 times 4. So it's technically 2 times the square root of 17. Now, again, if you punch this into a calculator, you know, who cares? But I'm just writing this down for the sake of our tutorial, okay? Now, the magnitude of the vector v, we're going to have what? You're going to have the square root of 3 squared is 9, then plus negative 5 squared is 25. So this is going to be the square root of 34. Now, you can't simplify the square root of 34, so let me erase this. I'm going to write this as the square root of 17. Okay, let me write this like the square root of 17 times the square root of 2 like this. Okay, so let's punch into the calculator. First, let me do this. Cosine of theta is equal to, again, you've got your dot product, which is the u dot v. Okay, so the vector u dot the vector v over, you've got the product of these two magnitudes. Okay, so the magnitude of this vector u times the magnitude of this vector v, okay? And then if I plug in to my calculator, what I want to do is say theta is equal to cosine inverse of all of this, okay? So the dot product of u and v is 46 over, you're going to have the magnitude of u times the magnitude of v. So essentially what you have is 2, okay, times square root of 17 times square root of 17 is 17, okay? So that's just going to be 34, okay? And then times the square root of 2. Now, again, you don't have to go through all this. If you were writing this out on a test, you might want to, but for the purposes of punching it into a calculator, who cares, right? It's just going to work either way. So, again, if you're having problems with this, wrap this in some parentheses. And if I punch this into my calculator, I get a theta that's approximately 16.93 degrees. All right, so before we wrap up the lesson, let's talk about the concept of orthogonal vectors. And this is just a fancy word to say that you have perpendicular vectors, okay? So they're going to meet at a right angle. So when the dot product for two non-zero vectors, again, u and v, is 0, then what's going to happen is the top part of this formula here is 0. And because you have non-zero vectors down here, the bottom part, or the denominator, will not be 0. So 0 divided by something that's not 0 is always going to be 0, okay? So then you could say the cosine of theta is going to be equal to 0. And where does this happen? Again, if theta is greater than or equal to 0 degrees and less than or equal to 180 degrees, well, it must be true that theta is equal to 90 degrees. So the angle between these two vectors, u and v, is going to be 90 degrees, meaning these two guys are perpendicular vectors, or in the language of vectors, we say they're orthogonal vectors, okay? So all you need to do, if you want to check to see if you have these orthogonal vectors, is just do the dot product and see if it's 0. Okay, that's all you want to do. So to start out this problem, I have this vector u, which is going to be 4 times the unit vector I plus 8 times the unit vector j. And then I have this vector v, which is going to be 6 times the unit vector I minus 3 times the unit vector j. Okay, so if I wanted to find out if these two vectors were perpendicular, or again, if they were orthogonal vectors, I could just find the dot product and see if it's 0. Okay, so in other words, with your formula, cosine of theta is equal to, you've got your dot product, okay, which is the dot product of u and v, so u dot v, okay, over the magnitude of this vector u times the magnitude of this vector v. Okay, so we know this formula at this point. Again, if this top part ends up being 0, and these guys down here aren't 0, which they won't be, well then the cosine of theta will be equal to 0, and theta is 90 degrees, right? So these guys are going to be perpendicular. So the dot product here, okay, we do u dot v is equal to 4 times 6 is 24, and then plus 8 times negative 3 is negative 24. So of course this is 0, right? So again, this top part would be 0. The bottom part wouldn't be 0. You can go through and find the magnitudes multiplied together, and you'll see that you're still getting 0, right, in the end. So 0 divided by something that's not 0, you just get 0, right? So the cosine of theta is going to be 0. So theta equals 90 degrees. And of course, we have perpendicular vectors. If you want to see this, your vector u, okay, which we have right here, the terminal point is at 4, 8, right? Because again, this vector u was set up as 4i, okay, that unit vector, plus we had 8j, that unit vector, okay? And then for the vector v, the terminal point was at 6, negative 3. So here's the vector v. Again, you're going to have this 6 times the unit vector I, plus you're going to have this negative 3, or might as well just write minus 3 times the unit vector j. Okay, so this is how we set this up. So this guy has a terminal point at 6, negative 3. This guy has a terminal point at 4, 8. You can see this graphically that they're going to meet at a 90-degree angle, and therefore, by definition, these guys are perpendicular, or you could say they're orthogonal vectors. All right, as a last example, what if you had something like this? So we have our vector u, and it's equal to, we have 7 times the unit vector I plus 7 times the unit vector j. Then we have this vector v, and it has b, okay, some unknown, times the unit vector I minus 8 times the unit vector j. How could I find a value for b such that the two vectors u and v would be orthogonal, or you could say perpendicular vectors? Well, all you'd want to do is just set up your little dot product, okay? So the dot product of u and v is going to be what? 7 times b, so 7 times b, and then plus, you're going to have 7 times negative 8, which is negative 56. So you really need this guy right here. You can just substitute this with a value here. You really want this to be 0. Let me just do this down here. So you really want this to be 0 so that those guys can be orthogonal vectors, right? So I'm just going to solve this equation for b. And to do that, I'm going to add, let's just go ahead and write this as negative 56 or minus 56. So I'm just going to add 56 to both sides of the equation, okay? So this would be gone. Let me just write this as 7b is equal to 56. Obviously, this is very simple. Divide both sides by 7. You'll find that b is equal to 8. Okay, very, very easy to do these. And again, if you plugged in an 8 there, well, then the dot product from your vector u and your vector v, so u dot v, would be what? 7 times 8 would be 56. And then plus 7 times negative 8 would be negative 56. So the dot product would be 0. And in this case, if b is 8, well, you would have perpendicular vectors, or again, orthogonal vectors. In this lesson, we want a review of complex numbers. All right, so I want to start out by talking about the imaginary unit I again. So we say I is equal to the square root of negative 1. And this is used to allow us to simplify when we have the square root of a negative number. So for example, if I had the square root of, let's say, negative 4, using the product rule for radicals, I could write this as the square root of negative 1 times the square root of 4, okay? I know that the square root of 4 is 2, so let me just go ahead and put the square root of negative 1 times 2 like this. And then I can replace the square root of negative 1, okay, since those guys match up with this I here. Okay, so this can go right there. So this is I times 2, or you just write 2I. Okay, so that's a way to simplify the square root of a negative number. Now also, let me erase all this. We can square both sides and come up with another definition. We could say that I squared is equal to negative 1. And we're going to use this all the time, okay? Now, using this imaginary unit, we can form what's known as a complex number. So the complex number in standard form is going to look like this. You're going to have a, which is your real part, plus b, which is going to be the imaginary part, times I, which is the imaginary unit. Okay, so let me label this real quick. This a is called the real part. Okay, and then the b here is called the imaginary part. Okay, now some books will call bi the imaginary part. Just get with your book or your teacher in terms of what they want to do if you get this for vocabulary. Now, in terms of complex numbers, we don't often think about it this way, but if you just had the number, let's say 3, well, 3 is a complex number, okay? 3 is a complex number because I could always say 3 plus 0i. It's kind of like when you think about 3 as being a natural number, right? It's a whole number, and then it's an integer, and then it's a rational number. And the way you show it's a rational number is you go, okay, well, 3 is equal to 3 over 1, right? Those are the same. So this is, by definition, a rational number. So it's the same kind of trick here where we just say, okay, well, 3 is really equal to 3 plus 0i because this is just 0, and 3 plus 0 is still 3, okay? So this tells me that any real number that I'm working with is also a complex number. So the real numbers are a subset, okay, of the complex numbers. And if you have a complex number, okay, like let's say 4 plus 2i, this is called a non-real complex number. That's how you can differentiate between the two. Also, you can have something that's called a pure imaginary number. Let's say you just had the 2i part. Okay, so this you could write as 0 plus 2i, which is just 2i. This is also a non-real complex number, but a lot of books will call this a pure imaginary number. Okay, let's go ahead and look at some examples. We're just going to fly through these. Again, this is just stuff we've already seen. If you wanted to simplify the square root of something like negative 147, you would use your product rule for radicals. I would just put this negative 1 here times, you would try to factor this. Well, 1 plus 4 is 5. 5 plus 7 is going to be 12. I know that 12 is divisible by 3, so 147 will be divisible by 3. And if I divide 147 by 3, I'm going to get 49. So I can put a 3 here, and I can get a square root of 49 here, okay? And this guy is a perfect square. So the square root of 49 is 7. So what I can do here is say that this is equal to square root of negative 1 times square root of 3, okay? Then times 7. Now this guy right here I can always replace with I. So really I'll end up with just saying that I have 7i, okay, times the square root of 3. So this would be our simplified answer for this square root of negative 147. Again, 7i times the square root of 3. All right, another similar problem, we have the square root of negative 180. So for this guy, if I think about 180, I would factor this. So 1 plus 8 is 9, so I know it's divisible by 9, so let me go ahead and put 9 there, and this would be 20, right? So 9 is 3 times 3, those are prime. 20 is 4 times 5, 4 is 2 times 2. So what I'd want to do, since 9 is a perfect square and so is 4, multiply those together, you have 36. So basically you'd want to write this as square root of negative 1 times square root of 36 times square root of 5. Okay, so that's going to allow you to simplify. And basically square root of 36 is 6, and square root of negative 1 is I. So I'm just going to put that we have I times 6, or I should really rearrange this and put 6i, and then just times the square root of 5. Okay, so simplifying these types of problems, very, very simple. This is our answer. Again, the square root of negative 180. This is going to simplify to 6i times the square root of 5. All right, so additionally, you will see complex numbers when you work with equations such as a quadratic equation. We know that if the discriminant, that b squared minus 4ac part, if that's less than 0, you're going to get complex solutions, okay? So we're going to see that here. So I'm just going to solve this. I'm going to use the quadratic formula. If you want to complete the square, you can do that on your own. So I have 2x squared plus 10x plus 5 equals 8x. I'm going to subtract 8x away from each side to put this in standard form. So this is going to cancel over here and be 0. So I'm going to have 2x squared plus 2x plus 5 equals 0. And basically, I'm going to record the values for a, b, and c. Okay, so what's a? It's the coefficient for x squared. So this guy right here, so that's a 2. And then what's b? It's going to be the coefficient for x to the first power, so that's also a 2. And then what's c? That's going to be your constant term, so in this case, that's 5. Okay, and then you're going to plug in. So x equals, remember this is negative b, plus or minus the square root of b squared minus 4ac all over 2a. Okay, this is something I've memorized throughout the years. If you don't have this committed to memory, it's okay. Something you can really look up quickly. Okay, so I'm just going to scroll down a little bit, and I'm going to plug in. So x is equal to the negative of 2 plus or minus the square root of, you're going to have 2 squared minus 4 times 2 times 5. And all I'm doing is I'm just plugging in, okay? This is over 2 times 2. So I plugged in for B, A, and C, and that's where we got this from. Now, let's just go ahead and solve this real quick. It's just a matter of punching this into your calculator. So x is equal to negative 2 plus or minus the square root of, you have 2 squared, which is 4, minus 4 times 2 is 8. 8 times 5 is 40. Go ahead and do 4 minus 40. That's going to be negative 36. And you can see because this part right here ends up being negative, you're going to have these complex solutions, okay? Then this is over the 4 because 2 times 2 is 4. And then the square root of negative 36, you can say that is 6i, right? Square root of 36 is 6, and then square root of negative 1 is I. Let's come down here a little bit, and let's go ahead and say that x is equal to negative 2 plus or minus, I'll put 6i over 4. Now, we can factor out a 2, okay, and make this a little bit better. So let's go ahead and say x is equal to, let me pull this down here a little bit. I'll factor out my 2. I'll have negative 1 plus or minus 3i, okay, then over 4. I'm going to cancel this with this and put a 2 here. So we'll say x is equal to, you have negative 1 plus or minus 3i over your 2. Now, if you want to write this in standard form for the complex number, then you could put this, we'll go ahead and do solution set notation. I'll put negative 1/2, okay, like this. And then I'll go plus or minus, we'll do 3/2 and then times I like this. Okay, so that's your solution set notation. Maybe I can make those brackets a little bit better. Let me try to make this one a little bit better like that. Okay, and of course, this is two different solutions, right? You have negative 1/2 plus 3/2 times I, and then you have negative 1/2 minus 3/2 times I. All right, let's start working on some operations with complex numbers now. So the first thing I'm going to do here is a simple multiplication problem. I'm doing this to draw your attention to a common mistake. So we know with the product rule for radicals, something like square root of A times square root of B, this equals the square root of AB. This only works when they're both not negative, okay? So if you try to do this here, you're going to end up with the wrong answer. So what you have to do when you have negatives involved like this, you have to convert them over, okay? Simplify first, and then go through a multiply. So what I would do here is I would say this is I times the square root of 3, then times, for this one, let me go ahead and write this out. So we'll have 2 times, I'm going to put the square root of negative 1 times the square root of 4 times the square root of 2, okay? Just so you can see what I'm doing. Square root of 4 is 2, so 2 times 2 is 4, okay? And then basically you would have square root of negative 1, which is I. So this becomes 4i times the square root of 2, okay? So from here now, if you multiply, you see that you have I times 4i, which is going to be what? That's going to be 4i squared, okay? Square root of 3 times square root of 2, we can write as the square root of 6. Now, what is I squared by definition? Remember, earlier we said this is negative 1, so you can say you have 4 times negative 1 times square root of 6, which is just going to be the negative of 4 times the square root of 6. Now, you'll notice if you didn't follow this formula, okay, and go ahead and convert this first, you would end up with the wrong answer, right? You would end up with a positive 4 times the square root of 6, which is not the correct answer. Okay, so you want to make sure you convert these over, simplify them first before you multiply. Okay, let's look at some addition of complex numbers. Really, really easy topic. To add two complex numbers, so for example, if I have a plus bi, and then I add this to, let's say, c plus di, okay? This is what? Add the real parts, so a plus c, okay? And then plus, you're going to add the imaginary parts, so we'll say b plus d, okay? And this is multiplied by I. That's all it is. If you were subtracting, okay, so if this was a minus, then this would become a minus, and this would become a minus, and that's basically it. Now, when you subtract things away, remember you can do addition of the opposite. So you could always go plus and then minus like this, okay? So if you want to do that, you can do that. Either way, your answer is going to be the same, okay? So let's go ahead and get rid of this, and let's work on this problem here. So we have 4 plus 2i plus we have negative 7 plus 7i. Okay, so what do? We add the real part, so 4 plus negative 7. Let me show this. So 4 plus negative 7, okay? And let me put a parenthesis there, and then plus. You add the imaginary parts, so 2 plus 7, so 2 plus 7, okay, then times I out here. And let's go ahead and simplify this. So 4 plus negative 7 is negative 3, and then plus 2 plus 7 is 9, and then times the imaginary unit I. So this is your answer here, okay, and it's in standard form, so negative 3 plus 9i. All right, for the next problem, let's do a subtraction. So you can do this as addition of the opposite if you want. So I'm just going to go ahead and say this is 7 plus 2i, okay. I'm going to say plus, and I'm going to change the sign of everything inside. It's just like if I put a plus here and a -1 outside and distributed this to each term, okay? That's all I'm doing, okay? I think it makes it a little bit simpler. So I'm going to change this to +5, and I'm going to change this to positive. I'm going to write a 1 and then times I. Remember, if something's hanging out by itself like x, you can put a 1 in front as the coefficient, okay? So now I can just add. So this will be 7 plus 5, okay? And then plus, you're going to have 2 plus 1, okay, and then times I. So this gives me 12 plus 3i as a result. And again, if you want to do this with subtraction, you can. It's going to look a little bit different. So what you can also do is you can say that you have 7 minus, in this case, this is a -5, so be very careful, okay? And then you have plus, you're going to have 2 minus, this is a -1, so again, be careful, okay? And then times I here. 7 minus a -5 is 12. And then plus 2 minus a -1 is 3, and then times I. So same answer either way. I think it's more straightforward if you do addition of the opposite. Let's look at some multiplication. Again, with these type of problems, you can generally use FOIL, okay? And sometimes you'll get longer ones just depending on the situation, but just pretend like you're multiplying polynomials, okay? So I'm going to use FOIL here. So I'm going to do the first terms. -4 times 2 is going to be -8. And then my outer, -4 times 4i would be -16i. My inner, I would do -3i times 2. That's -6i. And then my last, I would do -3i times 4i, which would be -12i squared, okay? So I squared is -1, so let's go ahead and replace that. So I'm going to have -8, and then I'll go ahead and move this down and say -12 times -1. Well, negative times negative is positive, so I might as well just say this is +12, okay? And then I have this, it would be -16i, -6i, so I can say that's -22i. So -8 plus 12 is 4, and then we'll say minus my 22i. Okay, so that's going to be my answer there. And I boxed it off a little bit too closely. So 4 minus 22i. All right, so we should know at this point about conjugates. If you have complex conjugates, the formula is a little bit different. So if we have something like a plus b times a minus b, we know this is a squared minus b squared, okay? As an example, let's say I have something like x minus 2, okay? Then I have x, let's say, plus 2. I know this is x squared, which is the first guy, minus 2 squared, which is the second guy, which is 4, okay? I don't need to FOIL this out. That's the quicker way to do it. But if I'm dealing with complex conjugates, the sign is going to change. It's not going to be minus, it's going to be plus. So for example, if I have a plus bi times a minus bi, what happens is a times a is a squared. The outer and the inner are going to cancel. And then the last, you have your minus b squared times I squared. Well, this I squared here is -1, and that's what's changing the sign. So you end up with a squared plus b squared, okay? So if I look at this pattern here, I have 4 plus 3i times 4 minus 3i. I can just say, okay, the first guy squared, 4 squared is 16, plus this 3 guy here, the second guy, just the b part, just the imaginary part. So the 3 guy squared, which is 9, so that's 25, okay? This is always going to be just a number. So in this case, it's just going to be 25, okay? Again, if you wanted to go through this the long way, we can. Just for the sake of completeness, we would do first times first. So 4 times 4 is 16. And then the outer would be -12i. The inner would be positive 12i. So you see those guys are still going to cancel. Then for the last, you have 3i times -3i. So that's minus 9i squared. And again, the I squared here is going to change the sign. And I circled that a little bit too widely. But basically, this is what? This is 16. You might as well say minus your 9 times -1, which is 16 basically plus 9, which again is 25. Okay, let's talk about dividing complex numbers now. So we know that if the imaginary unit I is in the denominator, since I technically is the square root of -1, it represents a radical, and it needs to be rationalized, right? So we want to rationalize the denominator when we see this situation. So if I have something like -3 minus 4i over 5 plus 4i, what can I do? Remember, we just talked about multiplying by the complex conjugate. If I multiply this by 5 minus 4i over 5 minus 4i, what's going to happen is in the denominator here, I'm going to have a real number now, okay? We don't care what happens in the numerator. We're trying to get the radicals out of the denominator. So in the denominator here, again, I can just take this guy. 5 would be squared. That's 25. And then plus This 4 would be squared, that's 16. So this ends up being 41. Okay, so that's the denominator now, so we're good there. In the numerator, you go through and just do FOIL, right? So negative 3 times 5 is negative 15. The outside would be negative 3 times negative 4i, which would be plus, we'll go ahead and say 12i. The inside would be negative 4i times 5, which would be negative 20i. Let's just go ahead and combine like terms. This would be a negative 8i, so a negative 8i. So I'll put minus 8i there. And then for the last, you have negative 4i times negative 4i. That's going to be plus 16i squared. I squared is negative 1, so let's get rid of this and just change the sign. So basically, I have negative 15 minus 16. So let's say this is negative 31. So the top here is negative 31, and then I'll put minus 8i, okay? Now, of course, if you want to write this in standard form, you want to break this up and say that you have negative 31 over 41. Let me put equals here. So this is the real part. And then we'll put, you can put plus, negative, or you can just put minus. I'll put 8 over 41 like this, okay? Let me make that 1 a little bit better. And then I'll put my I out here, okay? So this is your A, or your real part. And then this is your B, okay? Or your imaginary part, okay? Then you have your imaginary unit I. And of course, you could put plus, negative there if you want to. That's up to you. If you put minus there, it's really the same thing, so that's why I'm putting that. Okay, let's talk about simplifying powers of I, which is a really easy concept. Once you realize, you go through this little cycle. So I, the first power is just I squared is equal to negative 1. I cubed is I squared times I, right? So this is negative 1 times I, which is negative I. And then I to the fourth power is I squared. Let me make that better. So I squared times I squared, which is basically what? Negative 1 times negative 1, which is 1. Now, using this pattern, it's really easy to rewrite things, okay, in terms of one of these guys right here, and then you're just going to simplify. Okay, you can put that as your answer. So this involves the rules of exponents. So what I'm going to do here is I'm going to look at this right here. So this number is 151, okay? So thinking about what number going down would be divisible by 4. So I just take 151, punch this into my calculator, divided by 4, gives me what? Well, you're going to get 37.75, but I'm going to write this as 37 with a remainder of 3, okay? So basically, the 3 divided by 4 is where you're getting the 0.75 from. 37 times 4 is 148. So I can use that to my advantage. I can say, well, this is I to the power of 148 times I to the power of 3. So this is completely legal, right? I basically have just used my rules of exponents. We have I and we have I, so the same base. We would add exponents and we'd be right back to where we started. Now, what I can do, since this number right here is divisible by 4, I can use a little trick and I can say power to power rule, I to the fourth power raised to the 37th power, because again, 148 divided by 37 is 4, so 4 times 37 will be back to 148, right? This is power to power rule. Then times I cubed, okay? Now, why does this work? I to the fourth power, we see over here, is 1. So this guy right here is 1 raised to the 37th power, 1 to the 37th power. 1 to any power is always 1, right? So I can basically just get rid of this and say this is a big fat 1 now, times I cubed, okay? So I've dealt with that. And now I can just go to my little reference here and say, well, what's I cubed? It's negative I, okay? So that's basically what you want to do when you have a problem like this, when this guy's positive. All right, let's look at another example. So we have I to the power of negative 38. So there's a really easy way to do this, but let me do it the slow way first. I'm going to write this as 1 over I to the power of 38, okay? And then, of course, I can just do 38 divided by 4 and see where that puts me. It's going to be 9 with a remainder of 2, or 9.5. So really, I could write this. I could say this is equal to 1 over I. I'm going to go ahead and put I to the fourth power raised to the ninth power, okay? Then I'll put times 1 over, we'll go ahead and say I raised to the power of 2, okay? That remainder right there. Now, we know that this guy right here is 1, and 1 to the ninth power is 1. So I can just keep going like this and say this is what? This is 1 times 1 over I squared. I squared is negative 1, so I can say this is 1 times 1 over negative 1. So this just ends up being negative 1, okay? So really easy to simplify this, but this is kind of a long way to do it. The shorter way, if you're working with a negative exponent like this, well, now what I'm doing is I'm thinking about the smallest number that's divisible by 4, okay, that's going to be larger than this number. And I'm thinking about this in terms of its absolute value. So if you think about just the number 38, okay, going up, okay, what's the closest number that's going to be divisible by 4? Well, it's not 39, it's going to have to be 40, okay? So in other words, I would want to multiply this by, I would want to say I to the power of negative 38 times I to the power of 40. That's all I need to do, because what's going to happen here is that I to the power of 40 is just 1. I can multiply anything by 1, it's unchanged. So this is going to end up telling me that I have what? I to the power of negative 38 plus 40, okay, which is I to the power of 2, or I squared, which by definition is negative 1. So for me, this is a little bit quicker if I get this type of problem, but you can do it the other way if you'd like. All right, so the last thing I want to do is review a few things about the complex plane. So let's say we wanted to graph something like 5 minus 7i. What we'd do is set up a little complex plane. So instead of having x and y, we now have the imaginary, okay, which is vertical, and the real, which is horizontal. Okay, so before this was x and this is y, now this is imaginary, this is real. Okay, so if I have something like 5 minus 7i, well, again, this is the real part. We talked about this earlier. And then this right here, the 7 is the imaginary, okay, part. So all I need to do is move 5 units horizontally. Okay, 5 is positive, so I'm moving to the right. So I'm going to go 1, 2, 3, 4, 5. Okay, so right there. And then I want to move 7 units down vertically. Okay, so I want to move 7 units on the imaginary axis going down because it's negative 7. So 1, 2, 3, 4, 5, 6, 7, and it's going to put me right there. Okay, so this is going to be my 5 minus 7i plotted on the complex plane. Okay, so the last thing would be the absolute value of a complex number. So if we have something like the absolute value of 2 plus 6i, again, remember the way you would do this, this is going to be the distance between this number and 0, or the origin on the complex plane. Okay, so your distance formula normally is what? It's the square root of, you have x sub 2 minus x sub 1 quantity squared, plus you have y sub 2 minus y sub 1 quantity squared. Well, one of the points is at the origin, right? So it's 0, 0. So this is 0, and this is 0. So this is 0, and this is 0. So really, I can simplify this and say the distance between this guy and the origin is the square root of, drop the x sub 2 and just say x squared, plus drop the y sub 2 and say y squared, okay? Now, in the terminology of complex numbers, instead of saying x squared, I'm going to say a squared. Instead of saying y squared, I'm going to say b squared, okay? So what I'm going to do is say that the absolute value of some complex number, let's say a plus bi, is equal to the square root of a squared plus b squared. So this is the square root of 2 squared, okay, 2 squared, and make that better, 2 squared, plus this guy would be 6 squared. So this is the square root of 4 plus 36, so it's the square root of 40, okay, which is square root of 4 times square root of 10, which in the end, let me get rid of this so I have some room to write this. In the end is going to be 2 times square root of 10. So this equals 2 times square root of 10, okay? If you want to see this graphically, you could plot this guy, this 2 plus 6i, on the complex plane. So 2 units to the right on the real axis, 6 units up on the imaginary axis. So that gives us this 2 plus 6i, so that's this guy right here. And then basically what I'm doing is just forming a right triangle, right? So this guy right here, okay, is going to be my hypotenuse. That's what I'm looking for, is the length of that guy. So this is the absolute value of the 2 plus 6i, the absolute value of that complex number. And again, if you look at this distance from here to here, let me circle this in a different color. So let me use this color here. So from here to here, well, this is 6 units, right? So this is 6 units. Let me put a 6 there. And then if you look at the distance from there to there, it's 2 units. So again, with the Pythagorean theorem, it's 2 squared plus 6 squared is going to be equal to, which in this case would be the absolute value of 2 plus 6i, okay? We might as well just say that's squared, right? The a squared plus b squared equals c squared. Well, if I take the square root of each side, well, then I'm back to my formula, okay, which gives me the square root of 4 plus 36, which is the square root of 40, okay? And again, we just simplify that, so we know that in the end, the absolute value of this 2 plus 6i is going to be 2 times the square root of 10, okay? So you can see that graphically or just from using your formula. In this lesson, we want to learn about adding complex numbers graphically. Also, we'll learn about converting between rectangular and polar forms. Okay, so our first topic of adding complex numbers graphically is very, very easy to do. As long as you understand how to add vectors, you're basically good to go. So we return to our complex plane, which remember is also called the Argand diagram. And basically we replace the x notation here for the horizontal axis with real. we replace the y notation for the vertical axis with imaginary. So if you have a complex number like a plus bi, okay, where again, the a is known as the real part, okay, and the b is known as the imaginary, okay, part, well, basically I could use this to plot a little point on this complex plane, okay? I'm going to go a units horizontally, okay, and I'm going to go b units vertically, okay? So if I had something like, let's say, 3 plus 7i, well, the coordinates, if you're thinking about this as working on your regular xy coordinate plane where you have some value here, comma, some value here, well, it's 3, comma, 7. Right? I'm just moving 3 units on the horizontal axis. Now it's called the real axis. And I'm moving up 7 units, okay, on the vertical axis, now called the imaginary axis. So 3 units to the right, 7 units up would put me right there, okay? So I would go ahead and label this as the complex number 3 plus 7i, okay? If you wanted to do another one, let's say we do something like -5, let's say minus 4i, okay? So the coordinates there would be -5, comma, -4. So I'm just going 5 units to the left on the real axis and then 4 units down on the imaginary axis. So right about there, let's go ahead and say this is -5 minus 4i. For the purposes of making sure that you understand how to do this, you should pull out a sheet of paper and just make a rough sketch of an Argand diagram. We're going to use it throughout the lesson, so you might want to have that handy. And go ahead and pause the video and try to just graph this guy. Think about where it would be on your complex plane. All right, so hopefully you gave that a shot. This -7 plus 6i, again, the real part's -7, so I'm moving 7 units to the left. The imaginary part is 6, so I'm moving 6 units up. Okay, so 7 units to the left, 6 units up, which would put us exactly right here. Okay, so this would be your -7 plus 6i, 7 units to the left, and 6 units up. All right, now additionally, as you move higher in math, we start to think about graphing a complex number using vectors, okay? And specifically here, we're going to use a position vector or a vector in standard position, okay? So this just means that the initial point is at the origin. If you think about this in terms of a complex number, your origin is going to be at 0 plus 0i, or you could say 0, comma 0 if you want the coordinates, okay? So if the initial point's at the origin and the terminal point would be at this 8 plus 5i, so again, it's 8 units to the right and 5 units up, let's see this position vector graphically. So this would look something like this. Your initial point is at the origin, so right there. Your terminal point is at 8 plus 5i, so again, you're just going 8 units to the right and then 5 units up, and you have a directed line segment or a vector. Okay, so this is how we're going to show this 8 plus 5i when we're asked to graph it as a vector. All right, so now let's use the fact that we can graph a complex number as a position vector to show the sum of two complex numbers graphically. Okay, so we have this 6 plus 5i plus -9 plus 3i. Let's just add this together real quick, just so we know what we're supposed to get, and then we'll go to the coordinate plane. So we know we would add the real parts, so we do 6 plus -9. Okay, that's your first step. Then plus, we would add the imaginary parts. So 5 plus 3, okay? And this is multiplied by the imaginary unit I. So what I want to do here is do 6 plus -9, that's -3. And then plus, you have 5 plus 3, which is 8. And then times the imaginary unit I. So -3 plus 8i is your resultant vector. Okay, so let's look at this graphically. And again, you can do this with the parallelogram method or the triangle method, whatever you want to do. But essentially, you'll see here that we have the origin here, okay, which is our initial point for basically everything. Okay, so the 6 plus 5i, let's say you sketch that first. So here's the terminal point. Then you have this -9 plus 3i. Okay, so if we sketch that guy, that's the terminal point. And then again, if you want to do the parallelogram method, this guy gets shifted down to make this side here, okay, to make this side here. This guy gets shifted down to make this side here, okay? And this point right here is going to be your terminal point for the resultant vector. You see you get the -3 plus 8i. Again, if you want to use the triangle method, you can do that as well. Basically, you're going to shift this guy down here, so you would have that vector going like that, okay? And you would have your triangle looking like that, okay? So whatever you want to do, you can just show this graphically. I prefer this method because this is what's shown in most textbooks. And basically, you're keeping in line with the fact that this is a position vector, and this is a position vector, and then this is your resultant vector. All right, so what we want to do now is move into writing a complex number in what's called the trigonometric form, also known as the polar form, okay? So typically, we see our complex numbers written as a plus bi, where again, the a is the real part and the b is the imaginary part, or some books will say bi is the imaginary part. So what we're going to do is just switch this over to the x plus yi, where x is now going to be the real part and y is going to be the imaginary part. Now, in terms of notation, you're going to sometimes see that the I is switched. So you might see x plus I times y. This is done for clarity. Sometimes you'll have a radical involved. So you just have to be very, very careful when you have I written like this to understand what the imaginary part is, okay? That I is always separate from that. You have to remember that. And I'll show you that specifically here with some examples. Now, in terms of getting this guy from what we call rectangular form, which is the form that you normally see it in, the a plus bi or the x plus yi, into this polar form, you need to consider a few things. So we've graphed this guy as a vector, a position vector to be specific. So the initial point is at the origin, 0, 0. The terminal point is at the complex number x plus yi, or you could say the coordinates here are x, y, okay, on the complex plane. So if you think about a few things, first off, the length or the magnitude of this vector is labeled as r. We've seen this a bunch of times where we think about, okay, well, the length of this guy is the absolute value of the complex number, okay? Going back, we said the absolute value of a plus bi is the square root of a squared plus b squared. Again, this is just the Pythagorean theorem, right? If I go through here and I think about how to get the length of this r or the magnitude of this vector, well, this guy here would be r squared is equal to the length of this, which is x, so x squared, plus the length of this, which is y, so y squared. A squared plus b squared equals c squared. We're just going back to the Pythagorean theorem. If I take the square root of each side, I get that r is equal to the square root of x squared plus y squared. Okay, so this is something we're going to need today. When we want to find our r value, we just use this little simple formula. Again, if you can't remember it, it's just the absolute value of the complex number. That's all it is. So let's go ahead and cut this away, and let's just paste this on this little sheet here. We'll just go back and forth. So we also need to know about a few other relationships. So we think about this angle theta here, this direction angle for our position vector. The cosine of theta is what? So the cosine of theta is what? Remember, it's adjacent, which is x, over hypotenuse, which is r. And then we can also say that the sine of theta is what? It's opposite, which is y, over hypotenuse, which is r. Okay, let's grab these and cut these away and paste these in here. Again, we're going to be using this in a second. And basically what I want to do is I want to solve these for x and y, okay? So to solve this for x, I would multiply both sides by r, and I would have x is equal to r times the cosine of theta. To solve this for y, I do the same thing. I'm going to multiply both sides by r, so I would have r times the sine of theta, okay? So we're going to use this in a little while. Let's go back up. There's one other thing we need. So we recall when we work with vectors, we figure out the direction angle theta using the tangent, right? So we say that the tangent of theta is equal to y over x, where x is not 0, okay? So we're going to use this as well. But again, you remember from working with vectors, you have to be really, really careful with the inverse tangent function, okay? With the inverse tangent function, you're going to get something in quadrant 1 or 4 only. 1 if your argument is positive, and 4 rotating clockwise if your argument is negative. So let's come in here and let's paste this in. And I guess we can put that about right there, okay? So the polar form, let me just start with the rectangular form. So we have x plus yi. If you want to write yourself a little note and say, okay, well, this is a plus bi, just to keep track of this. Again, x is the real part, just like a. Y is the imaginary part, just like b. Okay, that's all it is. Just a little notational change. So this is the standard form, or the rectangular, I can never spell that, form. Okay. Then if you want the polar form, we're going to do a little bit of work. So let me do this on another sheet, and I'll actually come back. So we have the x plus yi, and I'm just going to be plugging in for x and y. If I go back, you see that x is r times cosine of theta, and y is r times sine of theta. I'm just going to plug in. So r times cosine of theta will be plugged in for x, and r times sine of theta will be plugged in for y. So r times sine of theta, okay? So what I'm going to do here, say this is equal to, I'll have r times the cosine of theta. Then I'm going to put plus, I'm going to put r times sine of theta. And I'm going to wrap this in parentheses just for clarity. This is going to be multiplied by the imaginary unit I. Okay, so again, this is x, this whole thing right here. And then this is y, this guy right here, and this multiplying the imaginary unit I. Okay, so I'm going to go a step further and just factor the r out now. So let me put equals, and I'm going to come down here with this. Let me drag a little arrow down here. If I factored out the r, where would I be? I would have r times, inside of parentheses, I would have my cosine of this theta, and then plus, again, I pulled out the r, I would have my sine of theta. But what I'm going to do is I'm going to put the I out in front. So I times this sine of theta, okay? And you have to be very, very careful when I is written this way, because sometimes it's going to get mixed up. And again, I'll show you some examples where you need to be careful of this, okay? So this is your polar form. That's all it is. Some books will abbreviate this, and they will put R times CIS. It's an abbreviation. So the C, then you have the I, and then the S. Okay, so that's how you can remember. R times CIS, and then times the angle theta. Okay, so if you want to write it as R cis theta, or write it like this is more popular. This is your polar form. So let me write this up here. We have R times, you have your cosine of theta, plus I times your sine of theta like this. This is your polar form. Or again, some books are going to call this the trigonometric form. And the shorthand for this is R times CIS of theta. All right, let's just look at some examples of converting back and forth between the two. This is a very, very easy process, but you do need to work a few examples so you get used to things, okay? You'll also see a lot of these come up over and over again because they're using values on the unit circle. So what I have here is 2 multiplied by the cosine of 150 degrees plus I times the sine of 150 degrees. So this is in the polar form, right? You have some value r here, which in this case is 2. And it's multiplied by cosine of some angle theta, in this case is 150 degrees, plus I times your sine of some angle theta, okay? So all I would do here basically is figure out what is the cosine of 150 degrees, what is the sine of 150 degrees, basically replace things, and then use my distributive property to distribute the 2 into everything, and you're going to have it in the format of x plus yi, okay, just like you want. So first and foremost, what is the cosine of 150 degrees? Remember, this has a 30-degree reference angle, and we're in quadrant 2. Cosine is negative, okay? And the 30-degree reference angle, cosine of 30 degrees, is square root of 3 over 2. So I can say this is the negative of the square root of 3 over 2, okay? Then the sine of 150 degrees, same 30-degree reference angle, but again, I'm in quadrant 2, so sine is positive. This is going to be 1/2, okay? And positive 1/2 at that. So all I need to do now is just go through and basically replace things. Let me get rid of this. I think we don't need this anymore. I'll say that I have what? I'm just going to put equals here. I'll say 2 times. Here I'll put the negative of the square root of 3 over 2. And then plus, I'm going to put the I here, okay, times, I'll put my 1/2, okay? Be very careful with the I. Again, it gets switched around a lot. Sometimes it's here, sometimes it's there. Just be careful with it. So let's just erase this. We don't need it anymore. And now I'm going to distribute the 2 to each term inside the parentheses. So I would have 2 times the negative of the square root of 3 over 2, and then plus, I'll do 1/2 times 2, and then you can do times I, okay? So basically we see that this would cancel with this, and this would cancel with this. And in my rectangular form, I have the negative of the square root of 3, basically plus 1i, or you could just say plus I, okay? So this is my rectangular form, or my standard form. And again, this right here is the polar form, or some people call this the trigonometric form. All right, let's look at another one. So we have the polar form here. We have 6 times. You have the cosine of 135 degrees plus I times the sine of 135 degrees. So what is the cosine of 135 degrees? So again, you're in quadrant 2, so this is negative. What is the sine of 135 degrees? Again, you're in quadrant 2, so this is positive. Remember, 135 degrees, you have a 45-degree reference angle. So in each case, you're going to have square root of 2 over 2, right? This guy's just going to be negative because cosine, again, is negative in quadrant 2. And this guy would be positive, okay? So basically, I can replace this and say I have 6 times. This is going to be the negative of the square root of 2 over 2. And then plus I times, you're going to have the square root of 2 over 2, okay? So if I distribute the 6 into each term, I would have 6 times the negative of the square root of 2 over 2 plus I times, let me go ahead and switch the order here so this makes more sense. We'd have the square root of 2 over 2 times 6 and times I. And I'll just go ahead and cancel this. This cancels with this and gives me a 3. This cancels with this and gives me a 3. So basically I'm going to have the negative of 3 times the square root of 2. And then plus you'll have 3 times the square root of 2 and then times I. Now again, a lot of times for clarity, you're going to move this around. Let me drag this down here so it's a little bit better so you can see things. I'll erase that and put that back in. Instead of having the I here, most books will do 3I like this, then times the square root of 2. This is just to make it completely clear that the I is not under the square root symbol. Okay, so the rectangular form here, or again the standard form, is negative 3 times square root of 2 plus 3I times square root of 2. And then again, your polar form, or the trigonometric form, is going to be 6 times this quantity, cosine of 135 degrees, plus I times sine of 135 degrees. All right, let's look at something more tedious now. So we're going to convert from our rectangular form to the polar form. I'm going to give you 3 easy steps for this. The first thing that I always do is I figure out what quadrant my complex number is in. You can do that by just thinking about the real part and the imaginary part. So in other words, if you were to graph this, again, on the complex plane, it's A comma B. So if this is positive and this is positive, then you're in quadrant 1. Okay, if this is negative and this is positive, I'm going left and then up, so I'm in quadrant 2. Okay, if they're both negative, I'm in quadrant 3, right? I'm going left and then down. And then lastly, if this is positive and this is negative, well, I'm going to be in quadrant 4, right? Because I'm going to the right and I'm going down. So just think about your real part and your imaginary part and ask yourself the question, if I was to graph this as a vector, okay, where would I be? Am I in quadrant 1, 2, 3, or 4? Okay, so that's the first thing you want to do. Now, if I look at this guy right here, I have 2 minus 2i times square root of 3. Again, this I is here for clarity. Okay, if you want to, you can write this as 2 minus 2 times square root of 3 times I. So it's crystal clear that this part right here is the real part, and this part right here, you can go ahead and take the negative with it, is the imaginary part, right? So A plus BI. Okay, so we know that the real part is 2, so that's positive. The imaginary part is negative 2 times square root of 3, that's negative. So I'm going to the right, okay, and then I'm going down. That means I'm going to be in quadrant 4, right? Because again, this is positive and this is negative, and you're thinking about this in terms of the complex plane. Okay, so now I know that theta is in quadrant 4. We need that for later on when we're getting our angle theta. So if we want to get this trigonometric form or the polar form, it's r times cosine of theta plus I times the sine of theta, okay? That's all it is. So I need to figure out what r is, and I need to figure out what theta is, and I'm done. So how do I figure out what r is? R, again, is just the absolute value of the complex number. Okay, we've been doing this forever. It's the square root of the real part squared, so 2 squared, plus the imaginary part. Again, if you're writing it like this, it's crystal clear. Negative 2 times square root of 3. So negative 2 times square root of 3, okay, this guy being squared. Some students make a mistake when it's written like this. Again, they put I in there for some reason. Again, just go ahead and write it like this so it's crystal clear that this is the imaginary part. You want the a squared plus the b squared, or the x squared plus the y squared, whatever the notation is, okay? The real part squared plus the imaginary part squared, okay? That's what you want. So we have r is equal to the square root of, this is 4, and then basically you have negative 2 squared, which is 4, and you have square root of 3 squared, which is 3. So 4 times 3 is 12. So I'd put plus 12 here, okay? So r is equal to the square root of 16, so r is equal to 4, okay? So the first part of that, okay, the first part of that is done. So r is equal to 4. And this looks like I made a radical here. I was just making a border. So let me kind of clarify that and put this maybe like this or something. That would be better, I think. And maybe I can just do it upside down. I'm just trying to make a border. That's not a radical. So r equals 4. Okay, so now I need to find theta. So what is that going to be? Again, you use the fact that the tangent of theta is y, okay, or the imaginary part, over x, or the real part, okay? So the imaginary part, you have your negative 2 times square root of 3 over your real part, which is 2, okay? So you can go ahead and cancel this with this, and this is the negative of the square root of 3, okay? Now what I would do, okay, is not punch this into the calculator as the tangent inverse of negative square root of 3, because you're going to get something in quadrant 4 rotating clockwise. Now, your teacher may allow that as an answer, but typically you want something between 0 and 2 pi, where 0 is included and the 2 pi is not, okay? So what I'm going to do is I'm going to say that I want the tangent inverse of the square root of 3. And this is going to give me 60 degrees, okay? This is going to be my reference angle, and I'm going to be in quadrant 4, okay? Remember, we figured out we're in quadrant 4 for this reason. So in quadrant 4, if I had an angle with a reference angle of 60 degrees, to find that I would do 360 degrees minus 60 degrees, which gives me 300 degrees, or in terms of radians, it would be 5 pi over 3. So now that we've done all this work, okay, we are ready to write this guy in polar form. And I guess you can get rid of this. We don't really need it anymore. I'm just going to write this and say that basically this guy, and I'll just even erase this, would be the r, which is 4, times you would have cosine of your angle. So you can use either one you want. You can do it in radians or degrees. So 300 degrees. Then plus, again, I'm going to put I first, and then times your sine, okay, of that same angle, 300 degrees. If you want to write this with radians, all it is, I'll put equals again, so 4 times, you're going to do cosine of 5 pi over 3, okay, and then plus I times the sine of 5 pi over 3. So always go with what your teacher says. If they want radians or degrees, just ask them, okay? So we basically have this done, and also, if you wanted to, you can use that little abbreviation. Let me just show you that real quick. You could do, this is 4 times CIS. So again, the C, the I, and the S, that's where the abbreviation is coming from. And then times, let's just go ahead and say 5 pi over 3. All right, let's look at another example. So we have negative 2 times square root of 3 minus 2i. So again, the first thing you want to do is figure out what quadrant is theta going to be in. And again, you can speed this up at this point. Again, here's the real part. It's going to be negative. Here's the imaginary part. It's going to be negative as well. In other words, if you were to graph this, you would have negative 2 times square root of 3. This would be your location on the real axis. And then you would have negative 2. That'd be your location on the imaginary axis. So in other words, this is negative and this is negative. So I know I'm going to the left and down. So I'm going to be in quadrant 3. And I put equals here. I should just put is in quadrant 3. Okay, so we can keep that straight. Now, what I want to do is quickly find my value for r. I'm just going to make that a little bit more clean. So my quadrant 3, I'll just put for my angle theta. So for r, again, it's the absolute value of this complex number. However you remember it, remember it's the square root of the real part squared plus the imaginary part squared, however they're giving that to you, okay? So I'm going to take the square root of, I'll take negative 2 times the square root of 3 being squared, then plus I'll have my negative 2 being squared, okay? So from here, I know that basically negative 2 squared is 4, square root of 3 squared is 3. So 4 times 3 would be 12. And again, we already know this, so this is going to end up being 4, right? Because this is 12 plus 4, that's going to be 16. Square root of 16 is 4, right? But to go through the steps, this would be 4. Again, 12 plus 4 is 16. Square root of 16 is going to be 4. So r is 4, we know that. So let's find theta. This is the one that takes a little bit longer. So we know that tangent of theta, again, is y over x, or you could say b over a, if you think about this in terms of the traditional way we think about complex numbers. It's going to be the imaginary part over the real part. So the imaginary part is negative 2, so negative 2, and the real part is negative 2 times square root of 3. Okay, so this is going to cancel, and I'll have 1 over the square root of 3. If I rationalize the denominator there, so times the square root of 3 over the square root of 3, this is the square root of 3 over 3, okay? So basically, if I punched up the inverse tangent of square root of 3 over 3, I'm going to get something in quadrant 1. Remember, I'm looking for something in quadrant 3, okay? So let's go ahead and set this up. I want to go inverse tangent, okay, inverse tangent of square root of 3 over 3 like this. So you hit that up on your calculator, you're going to get 30 degrees, okay? And again, in quadrant 3, if I have an angle with a reference angle of 30 degrees, to find that, I would do 180 degrees plus 30 degrees, okay, which would give me 210 degrees. So theta is going to be 210 degrees. So now that we have all the required information, I can just put equals. I'm going to take my r value, which is 4, And I'm going to multiply by, again, you have your cosine of this angle, 210 degrees, plus I times the sine of this angle, which is 210 degrees. So that's basically it. That's your polar form. Now, if you want to write this with radians or write it as an abbreviation, you can keep putting equals. So 210 degrees in terms of radians would be 7 pi over 6. So you could say this is 4 times, you'd have the cosine of 7 pi over 6, plus I times the sine of 7 pi over 6. And again, one more time, this C, this I, and this S, you can use it to abbreviate. So you could say this is 4, and you go CIS or CIS, and then you'll say your angle. So again, you could do degrees or radians, whatever. We'll do 7 pi over 6. So another way to write it, this is the shorthand. All right, let's look at one more example. So we have the negative of the square root of 31 over 2 plus the square root of 93 over 2 times I. Again, just be careful. Sometimes they'll put the I up here because you're working with a radical. Just be able to separate the imaginary part from the real part. Okay, you need to know what those are, and you need to not get I mixed into that. Okay, so what I'm going to do here again is think about what quadrant am I going to be in. Okay, this is negative, this is positive. So I'm going to the left and I'm going up, right? So I'm in quadrant 2. So theta is in quadrant 2. Okay, very important to understand where I am. Now, once I understand that I'm in quadrant 2, again, when I go to find theta, okay, I'm going to basically get a reference angle and then use that in quadrant 2. Well, let's find r first because that's a little bit easier. So r equals, again, the square root of, take your real part being squared. So negative of square root of 31 over 2. We're going to square that, plus take this guy, the imaginary part, so the square root of 93 over 2, this guy squared. So r is equal to what? If I square this, I'm going to get 31 over 4. So the square root of, you'll have 31 over 4, plus this guy would be 93 over 4, okay? If you add those together, you're going to get 124 over 4. So 124 over 4, if you make that division, you're going to get 31, okay? You can't simplify that. 31 is a prime number. So basically, r is just the square root of 31, okay? So r is equal to the square root of 31. Okay, let's work with theta now. So the tangent of theta is what? It's the imaginary part, or y, or b, however you want to think about it. So square root of 93 over 2 over the real part, which is x, or basically a, however you want to think about that. I'm just going to flip this guy, because when you divide fractions, you multiply by the reciprocal. So I'll put the negative of 2 over the square root of 31. That's going to allow me to cancel this with this. I know that from the quotient rule for radicals, I can divide here. So 93 divided by 31 is 3. So I can basically say this is the negative, okay, the negative of the square root of 3. Now, we know from the first example, this guy is going to have a reference angle of 60 degrees. If I did the inverse tangent of square root of 3, I'm going to get 60 degrees. So because I'm in quadrant 2, what I want to do is I want to take 180 degrees, and I want to subtract the reference angle of 60 degrees, and that's going to get me to 120 degrees. So theta is 120 degrees here. Okay, so theta is 120 degrees, or in terms of radians, you could say this is 2 pi over 3. Okay, so basically I'm ready to set this up. I can go ahead and say this equals, and let me just drag this out of the way. Put this down here. I'll say my r value, which is the square root of 31, times, let's just go ahead and use degrees first. So I'll say cosine of 120 degrees plus I times the sine of 120 degrees, okay? And again, you can keep going, right? So if you want to put this in terms of radians, I'll put equals, I'll do square root of 31 times the cosine of 2 pi over 3, and then plus I times, we'll do the sine of 2 pi over 3, okay, like this. And lastly, if you want to do your abbreviation, take your r value, which is square root of 31, and then times that CIS, or the CIS, again, the C, the I, and the S. So CIS, that's how you can remember that, and then times your 120 degrees. In this lesson, we want to talk about the product and quotient theorems. All right, so in the last lesson, we talked about how to write a complex number in what we call the trigonometric form. Most people call this the polar form. And here what we want to do is learn how to quickly multiply or divide two numbers if they're in polar form using something called the product or also the quotient theorems, okay? So I'm going to start off with the product theorem, and basically we have these two generic complex numbers written in polar form, right? Remember, when you think about the r value, If it's as a vector, if you think about it that way, this is the magnitude or the length of the vector, or you could also think about it as the absolute value of the complex number. Okay, so that's the R value in each case. When you think about theta, okay, this is going to be, if you think about this as a vector, it's the direction angle. Okay, or if you think about it here, a lot of books will also call this the argument. Okay, so you hear that terminology. So here we have this R sub 1 times the quantity cosine of theta sub 1 plus I times sine of theta sub 1. Okay, then times we have this other complex number, so R sub 2 multiplied by the quantity cosine of theta sub 2 plus I times the sine of theta sub 2. Okay, so all I need to do to derive my little product theorem, okay, is just use some FOIL. So I'm going to start out by multiplying R sub 1 times R sub 2. So R sub 1 times R sub 2. Then I'm just going to set up some brackets here, and I'm going to put these two inside. So I'm going to go the cosine of theta sub 1 plus I times the sine of theta sub 1. And then I'm going to go cosine of theta sub 2, and then plus I times the sine of theta sub 2. Okay, so all we're going to be doing is FOIL, nothing fancy here. So I'm going to put equals R sub 1 times R sub 2, and then let me open up these brackets. And if we're doing FOIL, we're going to do the first term, so this guy times this guy. So this would be my cosine of theta sub 1 times the cosine of theta sub 2. Then I want to do my outer, so this one times this one. Let me go ahead and put plus. I have an I there. Let me put that out in front. And then I'll just do my cosine of theta sub 1 times my sine of theta sub 2. Okay, I'm going to put this down here because it's going to run off. So I'm going to put plus, and I'm going to erase this and this, and now we're doing the inside, right? So it's basically going to be, and let me change the color, this one times this one. So you would have I times the sine of theta sub 1 times the cosine of theta sub 2, okay? And then lastly, we have the L, right? So this guy times this guy. I times I is I squared. Now you can put plus I squared, but remember this is -1 by definition, so we're going to change this in a moment. Then you have your sine of theta sub 1 times your sine of theta sub 2. Okay, let me close the brackets there because this is being multiplied by all of those. Now, as I just said, I squared is -1, so we can erase this and just put a negative sign here. Okay, and now what I want to do is I want to group everything where the terms that have an I are next to each other and the terms that don't have an I are next to each other. So I want this one and this one to be next to each other. And then let me change my highlighter color here. I want this one and this one to be next to each other. Okay, so let me go ahead and do that real quick. I'm going to put equals R sub 1 times R sub 2. And then inside the brackets here, I'll go cosine of theta sub 1 times cosine of theta sub 2. And then I'm going to do minus, I'm going to go sine of theta sub 1 times sine of theta sub 2. Okay, and then we'll go ahead and say plus, let me scroll down and get a little bit of room here. I'll say I times the cosine of theta sub 1 times the sine of theta sub 2. And then I'm going to put plus, I have my I times the sine of theta sub 1 times the cosine of theta sub 2. Okay, so let me close the brackets there. Now, the reason we group these guys together is because to further simplify this or to get it into the form you're going to see in your book, you're going to use an identity. So if we go back to our little handout and we go to the sum and difference identities, I want to call your attention to this first one. So we have the cosine of some angle A plus some angle B. Okay, in our case, it's theta sub 1 and theta sub 2. Okay, so the cosine of A times the cosine of B minus the sine of A times the sine of B. Okay, so what we have is this guy on the right, and we want to transform it to what it shows on the left. Okay, that's perfectly legal. So what we're going to do is say the cosine of theta sub 1 times the cosine of theta sub 2, so it's just like having A and B, okay, minus the sine of theta sub 1 times the sine of theta sub 2. Well, we could write that as the cosine of, we'll have the theta sub 1 plus the theta sub 2, okay? So I'm just using that identity to make this more compact. So let me put my bracket there. Let me put my R sub 1 times my R sub 2. Let me scroll down just a little bit to get some room here, okay? And basically, what I want to do now is for this second part, where I have, let me highlight this guy plus this guy, I'm first going to factor the I out, okay? So I'm going to put plus, let me do this over here, let me put plus, I'm going to put an I there. And inside, what I would have is the cosine of theta sub 1, okay, times the sine of theta sub 2. And then you'd have plus, you'd have your sine of theta sub 1 times your cosine. I probably can't fit this, so let me move this down here. Let me move this down here. So times the cosine Let me make this a little bit better. So the sine of theta sub 1 times the cosine of theta sub 2. So then let me close the bracket off here. So that's officially done, okay? And basically you see once I factor this I out, that here we can go back and we see that we have sine of A plus B is the sine of A times the cosine of B plus the cosine of A times the sine of B. Well, we have the same thing, okay? It's the sine of theta sub 1 times the cosine of theta sub 2 plus the cosine of theta sub 1 times the sine of theta sub 2. Now, it's not in that order, okay? It's reversed here, but you could rewrite it, right? Because this is addition. So I could say the sine of theta sub 1 times the cosine of theta sub 2 plus the cosine of theta sub 1 times the sine of theta sub 2. Okay, it wouldn't matter. So let's go ahead and put equals. I'm going to rewrite that one as well. And I'll say that I have my r sub 1 times my r sub 2 inside of brackets. I'll have cosine of theta sub 1 plus theta sub 2. So then I'll say plus, I'll put my I here, and I'll do my sine of, I'll say my theta sub 1 plus my theta sub 2. Okay, let me close the brackets there. So this result here is what you're going to see when you look at your product theorem in your book. Okay, so basically you multiply the two absolute values together. That's all you need to do. That's going to give you your r outside. And then inside, when you're working with this guy, you'd have the cosine of, you're adding the two arguments together. So now it's the theta sub 1 plus the theta sub 2 plus your I times sine of, again, you're adding your two arguments together. So your theta sub 1 plus your theta sub 2. So most books will just say you're multiplying the absolute values and adding the arguments if you want a simple way to remember that. Now, another way you might see this, again, in compact form, we might see this r sub 1 times the c I s, or the cis, right? That comes from this, the cosine, the I, and the s. Okay, it's an abbreviation. Let me just erase that. So basically you have this r sub 1 times this cis, and I'll put theta sub 1. If it's multiplied by this r sub 2 times this cis, okay, and then theta sub 2, this is going to be what? Again, multiply these two guys together, these two absolute values. So this is r sub 1 times r sub 2. And then basically you would have your CIS, and then you're adding these two arguments together. So your theta sub 1 plus your theta sub 2. Okay, so this is the shorthand, probably a way easier way to remember it. All right, so to get things started, let's go ahead and take a look at a very simple example. We have these two complex numbers in polar form, and we just want to find the product. So we have 3 times this quantity. We have the cosine of 150 degrees plus I times the sine of 150 degrees. Then we're multiplying by, we have 3 times this quantity, cosine of 90 degrees plus I times the sine of 90 degrees. So again, the very, very easy way to do this is just to multiply the absolute values together. So the absolute value of those complex numbers. So the 3 times the 3, that's going to give me 9. Okay. And then I'm going to set this up. I'm going to go the cosine of, I'm going to add the arguments. So I'm going to add 150 degrees plus 90 degrees. Okay, that's all I want to do. So the cosine of 150 degrees plus 90 degrees. Okay, and then plus my I times, I'm going to do my sine of, it's the same thing, just adding the arguments. So 150 degrees plus 90 degrees. 150 degrees plus 90 degrees. Okay, so basically you're just going to simplify this. And I'm going to have 9 times, again, this quantity. Now it's going to be the cosine of 150 degrees plus 90 degrees is 240 degrees. So I'll say this is the 240 degrees plus I times the sine of, we'll say 240 degrees. And again, you can also write this using your abbreviation. So you could say that this is the 9 times the CIS, or the cis, right? The C, and then the I, and then the S. And then go ahead and take that argument, the 240 degrees, okay, that angle there. So this is another way to write it. And then additionally, they might ask you to give it back to them in rectangular form. So let me just erase this, and this, okay, and we'll do that real quick. So again, for rectangular form, you need to figure out what is this and what is this, and then you're going to distribute the 9 to each term inside the parentheses. So for a 240 degree angle, we have a 60 degree reference angle. So the cosine of 60 degrees is going to be a half, and the sine of 60 degrees is going to be the square root of 3 over 2, okay? But because I'm in quadrant 3, cosine and sine are both negative, so I can say that this is negative 1/2. And then for this one, I'll say it's negative square root of 3 over 2, so I might as well just say minus the square root of 3 over 2, and I'll just put my I behind here like this, okay? So from here, I'm just going to distribute the 9 to each term inside the parentheses. So I would have negative 9/2 like this, and then minus, the 9 gets distributed, so 9 times square root of 3 over 2 and then times the imaginary unit I. So of course, if they ask you for polar form, it's going to be this one, okay? And then if they ask you for the rectangular form, you need to go through and figure this out, and then you get this one. All right, so let's look at a slightly more tedious example. So what we're going to do here is we're going to have our complex numbers given to us in rectangular form. We're going to convert them into polar form just to get some practice. And then we're going to use the product theorem to find the product of those two complex numbers, okay? So what I'm going to do here, let me put equals. I'm going to convert this one into my polar form first. So to do that, my R value would be what? Remember, that's the absolute value of the complex number. So you're going to take the real part, which is negative of 2 times square root of 2, and you're going to square that. You're going to add that 2. You're going to have your imaginary part, which is also the negative of 2 times square root of 2, negative of 2 times square root of 2, okay, being squared, okay? So basically, if I think about negative 2 being squared, that's 4. The square root of 2 squared is 2. So in each case, you have 4 times 2, which is 8. So you're going to end up with 8 plus 8, which is 16, okay? So you basically have R is equal to the square root of 16, which is 4, okay? So I can say that R equals 4 here. Now for the argument, theta, or you could say the direction angle, if you think about this as a vector, the tangent of this theta is the imaginary part over the real part, right? The b over the a, or you could say the y over the x, however you think about this. So I'm going to take the negative 2 times square root of 2, negative 2 times square root of 2, over negative 2 times square root of 2. Well, this is basically going to be 1, right? So the tangent of theta equals 1. Okay. If we use our inverse tangent function, so tangent inverse of 1, what is this going to give me? Well, if I'm working with degrees, I'm going to get 45 degrees, okay? But this is not our answer, right? Because remember, we have to consider what quadrant we're in. This is just going to give me the reference angle. So in this particular case, this is negative and this is negative, right? So if I was to graph this complex number on the complex plane, I would go to the left and I would go down, right? So I'm in quadrant 3. So in quadrant 3, if I had a reference angle of 45 degrees, I would want 180 degrees plus 45 degrees, which would be 225 degrees. So theta here is 225 degrees, okay? So now that gives us the information to write this guy out. I can say that my R value is 4, and then my argument here, theta, is 225 degrees. So I'd have cosine of 225 degrees plus I times the sine of 225 degrees, okay? So the first one's done. Now we just need to do the second one. So again, let me put times here. For this one, the R value is the square root of, take the real part, so negative of the square root of 3. This is squared. And plus, take the imaginary part. You can write a phantom 1 in there. This is really negative 1. So I'll put negative 1 here, and this will be squared, okay? So basically, the negative of the square root of 3 being squared is 3. And negative 1 squared is 1. So you're going to have 3 plus 1, which is 4. So R is the square root of 4, which is 2. Okay, so let's put 2 here. And then again, for the direction angle theta, I think about the fact that the tangent of theta is the imaginary part, which is negative 1, over the real part, which is the negative of the square root of 3. Now, let me go ahead and get rid of the negatives. So I'm just going to erase that from here. And I'm going to rationalize the denominator. So square root of 3 over square root of 3, multiply by that. And this gives me a tangent of theta, which is going to be the square root of 3 over 3, okay? Let me erase this and actually make this a little bit more compact. So the square root of 3 over 3. So again, if you punch this into your calculator, if you do tangent inverse of square root of 3 over 3, you're going to get 30 degrees, okay? But again, this is going to be your reference angle because this is negative and this is negative. So again, I'm in quadrant 3, right? If I want to plot that guy, I'd have to go to the left and go down. So in quadrant 3, if I have a reference angle of 30 degrees, to find that I have 180 degrees plus 30 degrees, that's 210 degrees. So my R value is a 2, okay? Put my parentheses there. I'd have cosine of, I would have theta is 210 degrees here, okay? So 210 degrees plus I times the sine of 210 degrees, okay? And again, you can use radians if you want. It's just a matter of what your teacher's working with. I'm just going to work with degrees here for now. Okay, so now to find the product, again, multiply the absolute values. So 4 times 2 is 8. And then I'm going to set this up. I'm going to go cosine of, I'm going to add the arguments. So 225 degrees plus 210 degrees. So 225 degrees plus 210 degrees, okay? Plus I times the sine of, again, I'm just going to add the arguments. 225 degrees plus 210 degrees. So 225 degrees plus 210 degrees. Okay, let me close that down. So we'll say this equals 8 times, okay? This quantity here is going to be the cosine of 225 degrees plus 210 degrees would be 435 degrees. So I'll say this is 435 degrees, and then plus I times sine of, again, that 435 degrees. Now, for some teachers, this answer is fine. For others, they want you to give an angle that is between 0 and 360 degrees, or 0 and 2 pi if you're working with radians, where in each case the 0 is going to be included, and your 2 pi or 360 degrees is not going to be included. Okay, so basically you would subtract, since we're working with degrees, 360 degrees from each one of these to get your coterminal angle, and in this case it's going to give you 75 degrees. Okay, so I can say this is equal to 8 times the quantity, you have the cosine of 75 degrees, plus I times the sine of 75 degrees, okay? So just get with your teacher in terms of if you need to do that. Most books will go to this. Some books will leave it like this and say it's fine. So it's really up to your teacher. All right, now let's move on and talk about the quotient theorem. So again, I'm going to go through where this comes from. I know a lot of you find this quite boring, but it's good to be able to see where things come from. It also gives you a lot of practice with manipulating things. So let's say we had these two complex numbers in polar form, and now we want to do the division, okay? So we have this r sub 1 times the quantity cosine of theta sub 1 plus I times sine of theta sub 1 over r sub 2 times the quantity cosine of theta sub 2 plus I times sine of theta sub 2, okay? Let me set this up over here because we're not going to have room to do what we need to do. So this is r sub 1 times the quantity cosine of theta sub 1 plus I times, we have sine of theta sub 1. Okay, that's your numerator. Your denominator here, or what you're dividing by, your r sub 2 times the cosine of now theta sub 2 plus I times sine of theta sub 2. Okay, so the idea here is that you would multiply the numerator and denominator by the complex conjugate of the denominator. Remember, if you had something like a plus bi, the complex conjugate would be a minus bi. So here, you could go through and multiply, okay, the r sub 2 into each term, but you're going to end up factoring it back out. So all you really want to think about is the inside here, the terms are going to be the same, okay? It's just that the sign is going to be different. So what I'm going to do is I'm going to multiply by, I'm going to have this r sub 2, and then times the quantity, you're going to have cosine of theta sub 2, okay, so that's the same. This is going to be minus now instead of plus, and then the term is the same. So you have I times sine of theta sub 2. Again, the r sub 2 here would just be factored out if it was distributed in, so you can think about it as just being factored out there. Okay, so that's why it's out there. Okay, so I'm just going to write this in the denominator here. So r sub 2 and then cosine of theta sub 2 minus I times sine of theta sub 2, okay, like this. Now this is quite lengthy, so I'm going to do the numerator and denominator separately. The numerator is going to be very similar to what we did earlier. It's just that we're going to have a minus involved in some different places, so we're going to end up using some different identities. All right, so let's go ahead and attack the numerator and denominator separately. Let me copy this, and I'm going to go to a fresh sheet here, and let me just paste this in, okay, and my multiplication symbol's out of whack there. So if we go through here, again, we start this in a similar way to the last one. So r sub 1 times r sub 2, okay? And then inside of here, you would have this cosine of theta sub 1 plus I times the sine of theta sub 1, okay? And this would be cosine of theta sub 2, and then minus your I times your sine of theta sub 2, okay? So again, all we're going to be doing is some simple FOIL. So I'm going to go equals r sub 1 times r sub 2 like this. And I'm just going to FOIL things out. So first times first. So again, cosine of theta sub 1 and then times cosine of theta sub 2. All right, so the next thing we would do is the outer. So I would do this one times this one. So I'm going to put negative. I'm going to put my I out in front. And then the cosine of theta sub 1 and then times the sine of theta sub 2. Okay. Then I'm going to go, let me erase this. Then I'm going to go the inside, so this one times this one. So I'll go plus, I'll have my I, and then the sine of theta sub 1 times the cosine of theta sub 2. Okay, so far so good. Now I just need my last, so let me go ahead and highlight. This one's already done, and then this one. So I know this is negative. I have I times I, which is I squared. And then I have the sine of theta sub 1, and then times the sine of theta sub 2. Okay, let me close the bracket there. All right, so remember, I squared is negative 1. So this is like if we had minus a negative 1, which is basically like having plus 1. Okay, so you can change this you can change this to a big fat plus, okay? So from here, now what I want to do is I want to get my terms with I together and the terms that don't have I together. So in other words, like we did before, this will be with this, okay? And let me color this differently. This will be with this, okay? So we're going to arrange it in that way. So let me go ahead and put equals here. Let me slide down just a little bit and get some room going. I'll have my r sub 1 times my r sub 2. I'm going to open up the brackets. So the cosine of theta sub 1 times the cosine of theta sub 2, okay? Then I'm going to put this next. So plus the sine of theta sub 1 times the sine of theta sub 2, okay? And then I'm going to put, you have a minus here and a plus here. It's actually to our advantage to rearrange that, okay? You can put it like this, but in the end, you can rearrange it because you're going to need an identity. So I'm just going to put this as plus. I'm going to use this one first. So I'm going to say I times the sine of theta sub 1 times the cosine of theta sub 2. And then I'm going to put minus the I times the cosine of theta sub 1 times the sine of theta sub 2. Now, you saw that last time we ended up factoring the I out. So let's go ahead and do that again. So I'm going to wrap this in parentheses and I'm going to get rid of this, okay? And I'm going to wrap this in parentheses as well, okay? So now what I'm going to do is I'm going to go back and I'm going to think about an identity that would help me out here. So I have cosine of some angle, let's call it theta sub 1, times cosine of some other angle, theta sub 2. Then plus we have sine of some angle, theta sub 1, times sine of some angle, theta sub 2. If we go back, you see that cosine of a minus b follows that pattern, right? Cosine of some angle a times cosine of some angle b, then plus sine of some angle a times sine of some angle b. So I can use that to rewrite this. I'm going to go r sub 1 times r sub 2, and then inside of brackets here, I'll have cosine of, I'll go ahead and say now this is the theta sub 1 minus the theta sub 2. Okay, so that part is done. Now, when we look at this one, sine of theta sub 1 times cosine of theta sub 2 minus cosine of theta sub 1 times sine of theta sub 2. If we go back, that's this guy right here, right? Sine of a minus b. This is sine of a times cosine of b minus cosine of a times sine of b. That's why I had to rearrange things because it would have been this way, the minus first and the plus. You can always rearrange it, but it might not be obvious, so that's why I did that. So let's go back, and now let's write this as plus, don't forget the I, and then times your sine of, this is going to be your theta sub 1 minus your theta sub 2, okay? So go ahead and close this down. So this is your numerator. If you want to copy this, let me go ahead and copy this, and I'm back on this screen now, so let me come down a little bit. I'm going to put equals here, and let me go ahead and paste that in. And I already had an equals, so I'm doing it twice. So let me go ahead and move this over just a little bit. So I'm going to say this equals this. And actually, let me put this a little bit further down. And then I'm going to put this over. We now need to work on the denominator, okay? So let me go ahead, and actually I should probably have equals here to make this complete. And let me grab this denominator now. Let me copy it. Let's go to another sheet, and let me paste this in now, okay? And we don't need this, and I need a times here. Okay, so for this guy, what you need to realize is that you could first multiply your r sub 2 times your r sub 2. So that's going to give me r sub 2. I'm going to wrap this in parentheses for clarity. So this is going to be squared. And then we're going to have the cosine of theta sub 2 plus I times the sine of theta sub 2. Okay, then times the cosine of theta sub 2. Now minus the I times the sine of theta sub 2. So notice that you have these complex conjugates here, okay, because you have the same term here and here, okay, and then you have the same term here and here, and this looks really weird. It looks like a face, so let me make that like that. And then basically your signs are different, okay. So what I would do here is just use my formula. So I would go ahead and say this is r sub 2 being squared times, essentially I would do the first guy squared. So let me put this inside of parentheses. I would say cosine squared theta sub 2, okay? And then minus your second guy being squared. So if I squared I would have I squared. If I squared sine of theta sub 2, I would have sine squared theta sub 2, okay, like this. Now, what are we going to do from here? Just think about this for a second. Minus I squared, remember, this is negative 1. So this is basically like minus a negative 1, which is basically plus. Now, hopefully you see this right away. You have cosine squared theta sub 2 plus sine squared theta sub 2. What is that? That's 1. If you go back, you see for the Pythagorean identities, sine squared theta plus cosine squared theta equals 1, right? So here we have cosine squared of theta sub 2, whatever that angle is, plus sine squared of theta sub 2, same angle, whatever it is, okay? And so this is going to be 1. So I can say this is r sub 2 being squared times 1, which just equals r sub 2 being squared, okay? So if I go back up, this is going to be my denominator. So let me bring this down here. And I'm just going to put this over r sub 2, and this is squared, okay? So remember, this is multiplication here. This is being multiplied. You could wrap this in parentheses to make that clear. This is being multiplied by this. So I can cancel a common factor of this guy with this guy. So essentially what I have here, okay, is going to be what you're going to see for your quotient theorem in your book, your r sub 1 over your r sub 2, okay? So you're dividing the absolute values, and then times this quantity here, you have your cosine of, you're subtracting the arguments, okay? So I'm doing my theta sub 1 minus my theta sub 2, okay? Then plus I times the sine of, again, I'm subtracting the arguments. So theta sub 1 minus my theta sub 2. And again, if you want to write this in a more compact form, well, if you had r sub 1 times your cis of theta sub 1 divided by r sub 2 times your cis of theta sub 2, okay? What this would be equal to is your r sub 1 over your r sub 2 times your cis of your theta sub 1 minus your theta sub 2, okay? So let me go ahead and wrap that in parentheses. And that's basically the shorthand. I think this is the easiest way to remember things. And let's just go ahead and look at an example. All right, so what we'll do here, we'll have this 2 times square root of 7 times the quantity. We have the cosine of 7 pi over 6 plus I times the sine of 7 pi over 6. And this will be over, you have your 3 times the quantity of your cosine of 11 pi over 6 plus I times sine of 11 pi over 6. So of course these two complex numbers are in polar form, so we can immediately use this quotient theorem, okay? But to get a little bit of extra practice, let's write our answer in polar form first, and let's also go into rectangular form, okay? So let's go ahead and say this is equal to, I'm going to divide the absolute values. So I'm going to say 2 times square root of 7 over 3, okay? This is going to be times the quantity. What you're going to do here is you're going to have your cosine of, you're going to subtract these arguments. So I'm going to do 7 pi over 6 minus 11 pi over 6. And I'll take care of this in a moment. I'll just leave it like this for now. And then plus I times your sine of, again, you're doing the same thing. So 7 pi over 6 minus 11 pi over 6. Okay, so just like that. All right, so let me close this down so that's proper. Let's put equals here. Let me scroll down and get a little bit of room going. So let's go ahead and say we have 2 times square root of 7 over 3. Okay, let me make that 3 a little bit better. And then inside of here, I'll have the cosine of, if I do 7 pi minus 11 pi, that would be negative 4 pi, right? You already have a common denominator. So let's say this is negative 4 pi over 6. And of course, you can reduce the fraction. Each is divisible by 2. So this would be 2 and this would be 3. So this is negative 2 pi over 3, okay? Then I'll do plus I times sine of the same thing, right? It'll be your negative 2 pi over 3. Let me go ahead and write this down here like this. And let me go ahead and close the bracket there, okay? So again, some teachers will accept this. Some of them want you to find the coterminal angle. So what I would do here is I could say negative 2 pi over 3 plus 2 pi, right? Or if I want a common denominator, this would be, multiply this by 3 over 3. So this would be 6 pi over 3, okay? So 6 pi over 3. So your coterminal angle here would be 4 pi over 3. So you could really write this, and you could say that this is 2 times square root of 7 over 3. And then inside the brackets, I'll say this is the cosine of 4 pi over 3, okay? Plus I times the sine of 4 pi over 3, okay? So for your rectangular form, what we'll do is we'll have 2 times the square root of 7 over 3. We need to think about the cosine, let me make a border here, the cosine of 4 pi over 3, okay? So this is going to be 240 degrees if you convert it into degrees. So cosine of 240 degrees, if that's easier for you. Again, it's going to have a 60-degree reference angle, or pi over 3 in terms of radians. So if you think about cosine of 60 degrees, again, it's a half, right? And this angle here, 240 degrees or 4 pi over 3, that's going to be in quadrant 3. So we know cosine is negative there. So this would first be the negative of a half. So let me put some parentheses here and say this is negative 1/2. Let me put plus my I, so I don't forget it. If I think about the sine of 4 pi over 3, again, 60-degree reference angle, we know that it's going to be in quadrant 3. Sine is negative, so let me just go ahead and make that minus. And basically, pi over 3, the sine of that is going to be square root of 3 over 2, right? So it's the negative of the square root of 3 over 2. You can put the I out in front like this, or typically with this situation, I'll put it here. So we'll close that down now. And all I need to do is just distribute this inside to each term, right? So basically, I have 2 times square root of 7 over 3 times negative 1/2. And then minus, you'll have 2 times square root of 7 over 3 times square root of 3 over 2 times I, okay? So let's come down here and just simplify, and we'll have our rectangular form. So the 2's are going to cancel here. You'll have the negative of the square root of 7 over 3. And then minus, the 2's are going to cancel here. Square root of 7 times square root of 3 is the square root of 21. And then this is over 3, and of course times I. So here is your rectangular form if you're asked to give that answer. All right, for the last problem, let's go ahead and take a look at one that's a little bit tedious. So we have this 1 minus I times square root of 3. This is over. You have the negative of the square root of 14 over 2 minus, you have the square root of 14 over 2 times I. So you'll notice that this division here involves these two complex numbers in rectangular form. So what we're going to do is we're going to put these into polar form. We're going to use our quotient theorem, and we'll just leave our answer in polar form, okay? So let's start out by converting each one of these over. So I have 1 minus I times square root of 3. I'm just going to do this on a separate page. So 1 minus I times square root of 3. So the real part is 1. The imaginary part is the negative of the square root of 3, okay? So let's go ahead and say my R is going to be the square root of 1 squared, which is 1, plus the negative of the square root of 3 squared, which is 3, okay? So obviously this is 4, and the square root of 4 is going to be 2, okay? So let's put this as 2, okay? So now I need to find my theta, right? So my argument for this guy. And so the tangent of theta is going to be equal to the negative of the square root of 3 over 1, okay? Might as well just say it's the negative of the square root of 3. So let me go ahead and do the inverse tangent function, okay, with the square root of 3. Forget about the negative. Let's punch that into the calculator. So what you're going to get there is 60 degrees, or pi over 3 if you want to work with radians. Let's work with radians since we work with degrees for the multiplication examples. So I'm going to say this is pi over 3, or you can just put 60 degrees if you like working with degrees. Okay, so let's put that there. Now, this is going to be my reference angle. Let's think about this guy. The real part here is positive, so I'm going to the right. And then the imaginary part here is negative, so I'm going down, right? So I'm going to the right and I'm going down. That means I'm going to be in quadrant 4. So what I'd want to do is I'd want to subtract 2 pi minus this pi over 3, okay, to figure out what my theta is going to be, okay? You can write this as 6 pi over 3. So 6 pi over 3. And this is going to give me 5 pi over 3, okay? Again, if you wanted to do this with degrees, you do 360 degrees minus 60 degrees, you would get 300 degrees. So however you want to do that. So let's go ahead and write this. Since we have all the required information, I'm just going to say theta here. Theta is 5 pi over 3, okay? So in polar form, we know that this is 2 multiplied by the cosine of this 5 pi over 3, and then plus I times the sine of our 5 pi over 3, okay? Again, if you want to put 300 degrees in there, feel free, okay? So I'm going to get rid of this. Let's go ahead and look at the other one. So we have this negative of the square root of 14 over 2 minus the square root of 14 over 2 times I. So let's go back. So we have the negative of the square root of 14 over 2, okay? Then minus, let me put this down here so it's a little bit more consistent. We have this square root of 14 over 2 times I. So my R is going to be equal to the square root of, I'm going to take this guy. So it's negative in each case. Just forget about it. We're going to be squaring it. Let's go ahead and say it's the square root of 14 over 2 squared. Well, if I square the square root of 14, I get 14. If I square 2, I get 4. So this is going to end up giving me 14 over 4, okay? So 14 over 4, which is going to be 7 over 2. So you would have 7 over 2, okay, plus 7 over 2, okay? So this would end up giving me 14 over 2, which is 7, okay? So this will be the square root of 7, okay? So that's all that is. So that's my R value. Let me drag this up here so it's out of the way. So now let's figure out what is the theta, okay? So again, if you look at this, the real part and the imaginary part, in each case is the same thing, right? So if I did tangent of theta is equal to, if you did the negative of the square root of 14 over 2, then over the negative of the square root of 14 over 2, that's just going to end up being 1, okay? So if I did the tangent inverse of this guy of 1, I get 45 degrees, or in terms of radians, it's going to be pi over 4. Okay, so you can put that, or you can put 45 degrees, whatever you want to do. So for this guy, this is negative and this is negative. So I'm in quadrant 3, right? I'm going to the left and I'm going down. So in quadrant 3, I would want to take pi, and I want to add pi over 4 to get that angle. So pi plus pi over 4, or again, you could do 180 degrees plus 45 degrees, whatever you want to do, okay? So for this one, I'm going to multiply this by 4 over 4. So this will end up being 4 pi plus pi, which is 5 pi, and then over the common denominator of 4, okay? So this is 5 pi over 4, or 225 degrees if you're working with degrees. So let's put 5 pi over 4 like this. Let's get rid of all this. So in polar form, this guy is going to be, we have our square root of 7 multiplied by, we're going to have our cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. Okay, so this part's done. Let me copy this. Let's come back up to our problem, paste this in real quick. And I'm just going to get rid of this. And what I'm going to do is I'm going to put equals like this, and I'll just drag this over. And I missed something, so let me get all of this. Drag this over here. Let me put my little division bar, and I did that terribly. So let me try that one more time. And let me just scooch this down just a little bit so it lines up perfectly. All right, there we go. So now what I want to do is just use my quotient theorem. Okay, very easy at this point. So 2 divided by the square root of 7. So 2 divided by the square root of 7. Of course, you can rationalize the denominator there. I can multiply this by the square root of 7 over the square root of 7. So this is 2 times the square root of 7 over 7. So 2 times the square root of 7 over 7. So that's that part, that's done. And then basically what we want to do, times this quantity here, you have the cosine of, you're going to have 5 pi over 3 minus 5 pi over 4. And I'm making this terribly, so let me kind of edit this a little bit. So this is a 5 and this is a 4. And of course, we need a common denominator. Let's just stop and get this. So we need to go 3 and then 3. We need to go 4 and then 4. So this would be 20 pi over 12. This would be 20 pi over 12. Minus, it would be 15 pi over 12. So 15 pi over 12, okay? So this would give me what? It would give me 5 pi over 12. So the cosine here of 5 pi over 12. Then I'm going to have plus, I have my I times the sine of, again, it's the same thing. So the 5 pi over 3 minus the 5 pi over 4. So that gives us the 5 pi over 12, okay? So this is going to be our result in polar form. Again, if you wanted to figure this out in rectangular form, just evaluate the cosine of 5 pi over 12, evaluate the sine of 5 pi over 12, get those values, and then just use your distributive property here to set that guy up. In this lesson, we want to talk about powers and roots of complex numbers. All right, so in the last lesson, we talked about multiplying two complex numbers together when they're in polar form using something called the product theorem. So what we're going to do here is just go a step further, and we'll talk about these powers and roots of complex numbers. So what I'm going to do is I'm just going to start out with a simple complex number, something generic, in polar form. So I'm just going to write r times the quantity cosine of theta plus I times the sine of theta, okay? So remember, when we talk about r, that's the absolute value of the complex number. When we talk about theta, it's referred to as an argument, okay? If you think about the complex number as a vector, it's going to be the direction angle, okay? So let's say that I wanted to raise this to, let's say, the second power, right? So I'm squaring this, and basically what I would do here, I would just expand this, right? So this would be r times the quantity of the cosine of theta plus I times the sine of theta, okay? And I'm going to multiply by itself. So r times the quantity of the cosine of theta plus I times the sine of theta. So you can see here that you have r times r. Remember, you're multiplying the absolute values together. So this gives me r squared. Notice that this guy right here, this exponent here on r, matches this exponent here. Okay, so this is going to be important. Then times the quantity, you have cosine of, remember, you add the arguments. So theta plus theta is 2 theta. Then plus I times the sine of theta plus theta, you add the arguments, this is 2 theta. So I want you to notice some things. Again, this 2 here, this exponent matches this exponent here. And then this guy here inside the parentheses, it's multiplying the argument. So the general rule is whatever this exponent is, and this can be any real number. For today, we're just going to work with positive integers. But whatever this guy is, it's going to basically be your exponent on r, and then it's going to be multiplied by your argument inside the parentheses. Okay. Now I can do another one with you just to show you this. So let's say we did something like r times the quantity cosine of theta plus I times the sine of theta. Okay. Let's say now we cube this guy. Okay. So we know that this would be equal to basically this guy times another one. Okay. This guy times this guy would give me this guy. So I can go ahead and write r squared times the quantity cosine of 2 theta plus I times the sine of 2 theta. Okay. Then multiplied by one more of these. So r times the quantity cosine of theta plus I times the sine of theta. Okay. So what is this going to give me? Again, r squared times r is going to be r cubed. So r cubed. Again, notice this exponent here matches this exponent here. Okay. So basically after that, inside the parentheses, you're going to have the cosine of 2 theta plus theta is going to be 3 theta. Okay. Plus I times the sine of 2 theta plus theta is 3 theta. So again, this exponent here of 3 is going to be your exponent here in r. And then inside the parentheses is going to be multiplying your argument. Okay, and this should make sense because if I'm raising this to the third power or I'm cubing this, then basically I have 3 of these. So I have 1, 2, and then a third one, right? So it makes sense that I have 1, 2, 3 r's. So it's going to be r cubed, right? R times r times r. And then you have this one, and another one. So if you're adding the arguments, you have theta plus theta plus theta, which is 3 theta, okay? So that's what's going to work. If you raise this to the 4th power, you see the same thing, 5th power, 6th power, whatever you want to do, any real number. Okay, so formally, this is our theorem here. You can write this down for your notes. Basically, if you have some complex number in polar form, so let's say r times the quantity cosine of theta plus I times the sine of theta, and this is raised to some real number n. Okay, again, we're going to use just positive integers today. Then basically, you can say it's r to the power of n times the quantity. You have cosine of n times theta plus I times sine of n times theta. Okay, so this n is going to be multiplying your argument, and it's also going to be your exponent on r, or the absolute value of that complex number. Again, for the shorthand, remember this is the c, the I, the s. That's where this abbreviation comes from. So we have r to the power of n, and then you have this cis, the cis, some people say, and then we have n times theta. All right, let's jump in and look at an example. So we're going to start with something very, very easy. So we have the negative of 5 times square root of 3 over 2 plus 5 halves I, and this whole thing is being squared. Now, obviously this is in rectangular form, and since this is just being squared, you could expand this and just perform the operation that way. But what we're going to do is use our little theorem. So we're going to first write this in polar form, then we'll use the theorem, okay? So I'll say this is equal to, I'm going to put my r times the quantity cosine of theta plus I times the sine of theta, okay? And this is going to be squared, okay? So I'm going to fill out my r and my theta. So to get those, remember, your r, okay, which is the absolute value of the complex number, is the square root of, you're going to take your real part, which is the negative of 5 times square root of 3 over 2, and you're going to square this, and then plus you're going to take your imaginary part, which is 5 over 2, okay, and you're going to square this. So let me scroll down and get some room going, and we'll come back up in a minute. Basically, if I have negative 5 times square root of 3 over 2 squared, the negative 5 squared is 25. The square root of 3 squared is 3. 2 squared is 4. So this is 75 over 4. So let's just replace this and put 75 over 4. And that is a terrible 5, so let's fix that. And then the 5 halves squared is just 25 fourths. So let's put plus 25 fourths. Now, 75 plus 25 is 100, and 100 divided by 4 is 25, okay? And obviously, 25 is a perfect square. Square root of 25 is 5. Okay, so let's say this is 5. Now, let me come up here just a little bit. So let me scroll up just a little bit. And I'm going to erase this r, and I'm going to put a 5 in there for the actual value. And now I need to figure out what theta is. So lots of ways to think about this. Remember, your tangent of theta, if you're thinking about this as x plus yi, well, it's going to be y over x, okay? If you're thinking about this as a plus bi, then it's b over a. It's the imaginary part over the real part, okay? But you have to be careful about this because when you use your inverse tangent function, you're only going to get something in quadrant 1 if this guy's positive, and something in quadrant 4 rotating clockwise if this guy's negative, okay? So you got to be real careful here. So let's come up and think a little bit about this. So the y part is 5/2. Okay, so that's 5/2. Then I'm dividing by a fraction, so I'm going to multiply by the reciprocal. The x part, or the real part, is going to be the negative of 5 times square root of 3 over 2. I'm going to flip that, so I'm going to put 2 over 5 times square root of 3. Okay, I'm dividing fractions, that's why I did that. Okay, so what I would see here is that this would cancel with this, and this would cancel with this, so I have the negative of 1 over the square root of 3. Rationalize the denominator, this is square root of 3 over square root of 3. And so this gives me the negative of, you have the square root of 3 over 3, okay? So let's think about this for a moment. If I type this into my calculator, okay, as the inverse tangent of this guy, I'm going to get something in quadrant 4, and I'm also going to get a negative angle, okay? So it's going to rotate clockwise. That is not what I want, okay? So what I'm going to actually do is I'm going to do the inverse tangent of, I'm just going to make this positive, so square root of 3 over 3. This is going to give me my reference angle, okay? So if I punch this into the calculator, I get pi over 6, okay, if you want to work with radians, or you get 30 degrees if you want to work with degrees. Now, this is not my answer because I'm not in quadrant 1. Okay, let's get rid of this. We don't even need this anymore, okay? Let's think about where we are. If you were to graph this complex number on the complex plane, then basically you think about the fact that this is negative, so the real part's negative, and this is positive, right? So this is positive. So from the origin, I would go to the left and I would go up. That puts my complex number in quadrant 2, okay? So in quadrant 2, I want an angle with a reference angle of pi over 6 or 30 degrees, okay? So basically you can say theta is equal to, you could do pi minus your pi over 6, okay? And I can do 6 pi over 6 to get a common denominator. So this is 5 pi over 6, which is 150 degrees, right? If you wanted to do this with degrees, you do 180 degrees minus 30 degrees. So again, it's 150 degrees. So let's do 5 pi over 6. So 5 pi over 6. So that's the tedious part. So let's just erase this and this and go 5 pi over 6. Of course, you can put 150 degrees in there if you feel more comfortable with that. That's up to you. Okay, so now that we have this done, finding our result here is really easy, right? Using our little theorem, this r value here is raised to this power. So 5 is squared. 5 squared is 25. That's easy. Then times the quantity, the cosine of, this gets multiplied by this exponent. So we'll have, let me do this in a different color, 2 times 5 pi over 6, okay? Then plus, let me return to this other color, so plus your I times the sine of, again, it's going to be 2 times 5 pi over 6, okay? That's all it is. It's very, very simple. Most of the work is just putting it in polar form. So once we have this, we can think about, okay, well, this would cancel with this and give me a 3. This would cancel with this and give me a 3. So this is going to be 25 times the quantity. You have your cosine of 5 pi over 3, okay, plus I times the sine of 5 pi over 3, okay? And 5 pi over 3 is 300 degrees if you want to write it like that. Again, up to you. Now, this is the answer in polar form. If you want to put it in rectangular form, again, it's all over the place in terms of what your teacher would ask for. Let's just get a little quick practice with that. So the cosine of 5 pi over 3, again, the reference angle there is pi over 3, okay, or 60 degrees. So the cosine of pi over 3 is going to be a half, right? And cosine in quadrant 4 is going to be positive. So this equals 1/2. Now the sine of 5 pi over 3, again, pi over 3, if you think about the sine of pi over 3, well, that's going to be square root of 3 over 2, but we're in quadrant 4, so sine is negative, so this is the negative of the square root of 3 over 2, okay? So let's go ahead and replace these. I'll go ahead and say this is equal to 25 times, I'll say this is 1/2, so this is going to be 1/2, and then plus, you have I multiplied by, this is going to be the negative of the square root of 3 over 2. Probably better to kind of switch this around here and then maybe scooch this down a little bit for formatting. And let's close this down, okay? So let's go ahead and distribute this 25 in. So this would be 25 over 2. And then basically I have plus negative here. Might as well just write minus. It's a little bit easier. I'll say minus 25 times square root of 3 over 2. Now you can put your I out here, and then sometimes people put the I there. It's really up to you. It's very clear here that it's not under the square root symbol, so I would just leave it like this. So this would be your answer in rectangular form, your 25 over 2 minus 25 times square root of 3 over 2, and then times I. All right, let's look at another example. So this one I'm going to give it to you in polar form, make it a little bit quicker. So we have 2 multiplied by the quantity cosine of 7 pi over 4 plus I times the sine of 7 pi over 4. And this whole thing is raised to the 5th power, okay? So if it's in polar form already, it's super easy, right? This R value here, this 2, is going to be raised to the 5th power. So you have 2 to the 5th power. We know that's 32, but we'll just simplify that in a moment. Then inside the parentheses, you'll have your cosine of, again, this exponent here of 5 is going to be multiplied by the argument. So 5 times 7 pi over 4, okay? Maybe make these parentheses a little bit bigger. Then we'll go plus I times the sine of 5 multiplied by the 7 pi over 4. Let me close the parentheses there. So we'll say this is equal to, let's go ahead and say this is 32, right? 2 to the 5th power. Then times the quantity. 5 times 7 is 35. So this would be the cosine of, we'll say, let me make that S a little bit better. So we'll say this is 35 pi over 4. And then we'll say plus I, so plus I, times the sine of 35 pi over 4. Now again, some teachers don't care. You can leave this as your answer if they say we want it in polar form. That's really up to you. If you need to put it in rectangular form, it's kind of hard to do that with 35 pi over 4. I mean, I know we can use calculators, but if you wanted to think about this off the unit circle, for myself, I always like to put it between 0 and 2 pi, with 0 included and 2 pi not, okay? So if you think about 35 over 4, forget about the pi for a second, 35 over 4, that's really close to 36 over 4. 36 over 4 is 9, okay? So that tells me if I think about 2 pi, 4 pi, 6 pi, 8 pi, okay, I would want to subtract 8 pi off to get myself a coterminal angle. So if I did 35 pi over 4 minus 8 pi, of course I could write this as 32 pi over 4, 32 pi over 4, this is 3 pi over 4. Okay, so that looks a little bit easier to work with, so I'm just going to change this. Again, some teachers require it, some don't care. So 32 times the quantity cosine of 3 pi over 4. Let me make that a little bit better, okay? Then plus I times the sine of 3 pi over 4. Okay, so that's done. So if you want your answer in polar form, again, this one if your teacher doesn't care, this one if they do, okay? If you want your answer in rectangular form, well then again, I've got to go through and figure out, well, what is cosine of 3 pi over 4? And what is sine of 3 pi over 4? So if you're not used to working with radians, if you haven't memorized your unit circle, this is 135 degrees. So you know this is in quadrant 2. So sine is positive, okay? And this guy is negative. And remember, with 135 degrees, you have a 45-degree reference angle, or in terms of radians, it's pi over 4, okay? So for both of those, it's square root of 2 over 2 if you think about pi over 4, right? But this one's negative and this one's positive. So this would be the negative of the square root of 2 over 2. And this would be positive square root of 2 over 2, okay? So we would say that you have equals, I'll go 32 times the quantity. I'd have the negative of the square root of 2 over 2. And then plus you'll have your square root of 2 over 2 times I. Okay, again, the I gets changed around based on what book you're looking at, what teacher you're working with. Sometimes they put it out in front there. It's really up to you. So what I'm going to do here is just say that 32 is multiplied by this. 32 divided by 2 is 16. So this would be negative 16 times square root of 2. Okay, plus 32 times this, the 32 divided by 2 is 16. So I'm going to say 16 times square root of 2 and then times I. Now again, this is all over the place in terms of how the formatting goes. Typically with this, you'll see 16i and then times the square root of 2. Again, you don't want to think that it's underneath this square root symbol, so that's why this is done, okay? So this would be your answer in polar form right here, okay? And then in rectangular form, we say negative 16 times square root of 2 plus 16i times square root of 2. All right, so now let's talk about the roots of complex numbers. So I'm going to use this first example here to derive a little formula we can use. If you don't want to watch it because it's a bit tedious, you can just skip ahead to where we're doing the examples. So first and foremost, every non-zero complex number is going to have exactly n distinct complex nth roots. So you might read this in your book and think, what in the world does that mean? Well, what it means is that every given non-zero complex number is going to have exactly 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, so on and so forth. So what we can do is use this example here to come up with a little formula, okay? Let's say that I asked you to find the 3 complex cube roots of this number, okay? What does that mean? Well, let's just go back to regular numbers. Let's say I had just the number 8, okay? So the number 8. What if I wanted to find the cube root of that? Well, I'm looking for a number that when cubed gives me this number, okay? So we know this is 2, right? So 2 cubed gives me 8. So I'm going to do the same thing. I'm going to be looking for a number that when cubed produces this number here, okay? So all I'm going to do, let me just rewrite this. So I'll just say that 3 times the quantity cosine of, let's say, 45 degrees plus the I times the sine of 45 degrees is going to be equal to, again, I'm just going to take a generic complex number in polar form. So I'm going to say r times the quantity cosine of, I'm going to use alpha here instead of theta. So plus, I'll do I times the sine of, again, I'm going to use this alpha, okay? So now I'm just going to raise this to the third power. There is nothing different between this and what I just showed you with 8 being equal to 2 cubed, okay? I'm just taking this number, raising it to the third power. So this number right here is going to be a cube root, okay, of this number because raising it to the third power produces this. Just like 2 is a cube root of 8 because 2 to the third power is 8, okay? It's all it is. So from this point on, what I'm going to do is just simplify things and come up with a little formula, okay? So I'm just going to say 3 times the quantity cosine of 45 degrees plus I times sine of 45 degrees, okay, is equal to, if I use my theorem from earlier, r would be cubed, so r cubed, and then times the quantity cosine of, I'm multiplying the 3 by the argument, so 3 times my alpha there, plus I times the sine of 3 times alpha, okay? So in order for this to be true, you've got to think about the parts of this equation. So this would have to be equal to this, okay? And then this would have to be equal to this, and then this would have to be equal to this, okay? So in other words, r cubed would have to be equal to 3, which tells me if I take the cube root of each side, okay, the cube root of each side, that r is going to be equal to the cube root of 3, okay? And we'll see this in our little formula in a moment. For right now, this is what we have, okay? So let me bring this up here so that's out of the way. And then the next piece would be that the cosine of 45 degrees is equal to the cosine of 3 times alpha, okay? And then also the sine of 45 degrees is equal to the sine of 3 alpha, okay? So let's think about this for a moment. We know about coterminal angles, okay? And we know that, let's say the cosine of 45 degrees has the same value as the cosine of, if I added 360 degrees to that. So if I said the cosine of 405 degrees, this would be equal to the cosine of 45 degrees. And you can pause the video and punch into your calculator. You should know that those are equal. It's also equal to the cosine of a negative 315 degrees, okay, if you wanted to do it that way. Okay, so knowing this fact, what we could do is set 3 times alpha, so 3 times alpha, equal to this 45 degrees, okay, plus I'm going to do 360 degrees times some integer k, okay? Now, we don't have to consider negatives. I'm going to show you how solutions just keep repeating themselves. I'm just going to work with 0, 1, and 2, okay? And I'll show you that when you get to 3, 4, 5, 6, things repeat. Also, if you go -1, -2, -3, you're just getting repeat solutions, okay? So what I would do here is I would simplify this a little bit, and I would divide both sides by 3, okay? So both sides by 3. So I'd have that alpha is equal to 45 degrees divided by 3 is 15 degrees, okay? Then plus 360 degrees divided by 3 is 120 degrees, and then times k, okay? So to get the values for alpha, you're going to see in our little formula, you plug in, if I'm trying to find the cube root, then I'm going to plug in 0, 1, and 2. Okay, so I start with 0, then I go to 1, then I go to 2. If I was trying to find the fourth root, I would go 0, 1, 2, 3. So it's always 1 less than that number. Okay, so if it's 4, you're going to 3. If it's 5, you're going to 4. If it's 6, you're going to 5, so on and so forth. So let's go ahead and go through and say our first alpha would be 15 degrees plus 120 degrees times 0. So 120 degrees times 0. So this is basically going to be 15 degrees. Then another alpha would be 15 degrees plus 120 degrees times 1. So this is going to be 135 degrees. So 135 degrees. Then our other alpha is going to be 15 degrees plus you're going to do 120 degrees times 2. And this is going to give me 255 degrees. Okay. And then again, we don't need this, but if you did go to 3, so alpha is equal to 15 degrees plus 120 degrees times 3, Well, this is 360 degrees plus 15 is 375 degrees. 375 degrees and 15 degrees are coterminal angles, okay? So if I was to say the cosine of 15 degrees or the cosine of 375 degrees, it's the same, okay? So you don't need to go 3 and 4 and 5 and 6. You're just going to get repeat solutions, okay? So you don't need that. You also don't need to do the negatives because you're just going to get repeat solutions. So let me erase this. So coming back now, let me show you that these solutions work, okay? So let me box this off. Remember, originally we were looking for the 3 cube roots. So the 3 numbers that I could plug in here and cube them and get back to this number. So let me show you with the first solution for alpha. So we have our r value, which is the cube root, okay, of 3. And then it's multiplied by the quantity cosine of alpha. So one of those would be 15 degrees plus I times the sine of 15 degrees, okay? Let me get rid of this one. Then the next one would be the cube root of 3 times the cosine of, it would be 135 degrees, plus I times the sine of 135 degrees, okay? Let's get rid of this one. And then your last root here, so the last cube root, would be the cube root of 3 times the quantity, the cosine of 255 degrees, plus I times the sine of 255 degrees, okay? So let's get rid of this. Now, if you were to cube each one of these, you're going to get back to this right here. And we can just do it mentally. We don't need to actually go through it. If we cube this number here, again, following that theorem from earlier, this guy right here would be cubed. So cubing the cube root of 3 gives me 3. So it gives me back that number. Then if I multiply 3 times 15 degrees, I get 45 degrees. If I multiply 3 times 15 degrees, I get 45 degrees. So you can see that cubing this first one right here gives us this back. Now I'll let you do this one and this one on your own, just cube them. You're going to see that the angle you get in each case is going to be coterminal with this angle here that's 45 degrees. In this case it would be 405 degrees, and in this case it would be 765 degrees. Okay, so let's go from our example and make a nice little formula. So if n is any positive integer, and r is a positive real number, and theta is in degrees, then the non-zero complex number, let's say r times the quantity cosine of theta plus I times the sine of theta, is going to have exactly n distinct nth roots given by the following. So we're going to say that we have the nth root, okay, of this r. You saw earlier we were looking for cube roots, so we had the cube root, which was n was 3, of, in our case, it was 3. So it was the cube root of 3, okay? And basically, we're going to multiply this by the quantity. You'll have the cosine of alpha plus I times the sine of alpha, okay? And basically, what alpha is going to be, I'll do degrees first and then I'll do radians. So alpha is going to be theta, okay? So this guy right here, divided by your n. Okay, so you saw earlier, what we had was 45 degrees divided by 3, which gave us 15 degrees, okay? Then plus, you're going to do 360 degrees times k is just some integer, and I'll talk more about that in a second, divided by n. So in our example, you saw 360 degrees divided by 3, okay, which gave us 120 degrees. And then multiplied by k, where basically k is going to be equal to 0, 1, 2, 3. We'll put the 3 dots here to show the pattern continues, and then we'll go n minus 1, okay? So in our case, our n was 3, so we went 0, 1, 2. Then 3 would give us a repeat solution, so would 4, so would 5, so would 6, so on and so forth. Now, if you're working with radians, then you would adjust this formula, and basically instead of 360 degrees, you would just put 2 pi in there, okay, in terms of radians. Nothing else is going to change. So just depending on if you're working with degrees or radians, you would either want to use 360 degrees for degrees or 2 pi for radians. All right, let's go ahead and look at an example. So we want to find all nth roots, okay, and we're going to write our answer in polar form. So we see that n is set equal to 4, so we want to find the 4 fourth roots, okay? So I'm going to start by writing this guy right here, this negative 3 times square root of 3 minus 3i in our polar form, okay? And so let's go ahead and say that the r value would be what? The square root of, we take the negative of 3 times square root of 3, we're going to be squaring that, plus you're going to take your negative 3, okay, we're going to be squaring that. So the r is going to be equal to, we'll say the square root of, negative 3 squared is 9, square root of 3 squared is 3, 9 times 3 is 27. So this is 27 plus negative 3 being squared is 9. 27 plus 9 is 36. So r equals the square root of 36. So r equals 6. Okay, so we've got that part down. Let me go ahead and say that in polar form, this negative 3 times square root of 3 minus 3i would be equal to, I'd put a 6 there, times, you're going to have your cosine, okay, your cosine of theta, I'll replace this in a second, plus your I times your sine of theta, okay? So for theta, again, remember that the tangent of theta is equal to, take the imaginary part, so negative 3, over your real part, which is negative 3 times square root of 3. And so with this, we see the negatives are going to cancel, the 3's are going to cancel. So you have 1 over square root of 3. Again, rationalize the denominator. So square root of 3 over square root of 3. So this is going to be what? Square root of 3 over 3. So if I did my inverse tangent, so my inverse tangent here of square root of 3 over 3, let me make that 3 a little bit better. If we punch this into our calculator, you're going to get 30 degrees, or pi over 6 if you want to work with radians. Let's just work with degrees. So I'm going to say this is 30 degrees. So this is my reference angle. So let me erase this. And let's think about where this complex number would be if we graphed it. So this is negative, and so is this, right? So I have a negative real part and a negative imaginary part. So from the origin, I would go to the left, and then I would go down, okay? So that means I'm going to be in quadrant 3. So my theta here would be 180 degrees plus the reference angle of 30 degrees, which is 210 degrees, okay? So I can just erase this, and I'll go ahead and put 210 degrees there, so 210 degrees. Once you have this in polar form, it's just a matter of plugging into your formula. You want to do your nth root of r. So in our case, n is 4 and r is 6. So we want the fourth root of 6. So we want the fourth root of 6. And you're going to have 4 of these, but I'm just going to start out with the first one, okay? Inside of here, what are we going to have? We're going to have the cosine of, again, we call this alpha plus I times the sine of alpha, okay? And alpha, since we're working with degrees, alpha is going to be equal to, you have your theta divided by n. In this case, the n is 4. Plug that in a second. Plus, you have your 360 degrees divided by n times k, where we say that k is equal to, in this case, because it's 4, it's going to be 0, 1, 2, and 3. Okay, so you just go up to 1 less than whatever n is. That's all it is. So in our case, let's just plug this in. So n is going to be 4. So let's erase this and put 4 in each case. Okay, and then theta is coming from here. So it's 210 degrees. Okay, so let's put 210 degrees here. So if I divide 210 degrees by 4, it's going to give me 52.5 degrees. So 52.5 degrees. And then 360 degrees divided by 4 is going to give me 90 degrees. Okay, so 90 degrees. So basically, to set this up, the first one would be, again, if this guy was 0, plug that in, this is gone. So you just get 52.5 degrees. Okay, so you can put that in there. So 52.5 and 52.5. Now, you can pause the video and you can raise this to the 4th power, and you'll see that you get back to this guy right here. Okay, and then, of course, you can convert that back into rectangular form if you wanted to get back to that original form we started with. Okay, but let's go ahead and keep going. And basically, let me drag this down just a little bit. And I'm going to slide my screen just a little bit down, okay? And basically, now I'm going to do the fourth root of 6 times the quantity. I'll do the cosine of, and then I'll leave that blank for now, and then I times the sine of. And let me leave that blank for right now. So the next one would be, this guy would be 1 now. Okay, so I'm going to plug in a 1. So basically, 90 degrees times 1 is 90 degrees, and 90 degrees plus 52.5 degrees is going to be 142.5 degrees. And I forgot my degree symbol here and here, so let me put that in. So 142.5 degrees. Let me make that decimal point a little bit better. So from here, all I'm going to do is add on 90 degrees, okay, 2 more times. So I can just get rid of this, okay, once you understand the pattern. And basically, I can just copy this. And so 142.5 plus 90 is 232.5. So this would be 232.5 degrees. And this would be, again, 232.5 degrees. And then add 90 degrees again, and you get 322.5. So 322.5 and 322.5, okay? So this would be your 4 fourth roots for that number. I'm leaving these in polar form. All right, let's take a look at another example. I think this is going to be pretty easy for us at this point. But I want to throw something in here. Sometimes your book will ask you to graph the roots on the Argand diagram or the complex plane. So let's go ahead and do this. So we have -8 plus 8i times square root of 3. Again, n is going to be 4. So I'm looking for the 4 fourth roots. Now, again, this is given to us in rectangular form, so I need to convert it into polar form first, okay? So the r value times, again, the quantity cosine of theta plus I times the sine of theta. So let's do this quickly. So r is going to be what? The square root of -8 squared is 64. And then if you have 8 times square root of 3 being squared, it's 64 times 3, which is 192. Okay, so you're adding those two together. And that's going to give me 256. If I took the square root of that, I would get 16. Okay, so let's just erase this and put 16 here. Then for theta, it's going to be where? The real part is negative, so I'm going to the left. The imaginary part is positive, so then I'm going up. So from the origin, if I go to the left and I go up, I'm going to be in quadrant 2. Okay, so let's say that theta will be equal to 180 degrees minus my reference angle. And the reference angle here, let's go 8 times square root of 3. And I'm going to divide that by, forget about the negative, let's just do 8. This is going to cancel with this, so this is square root of 3. Okay, so I'm going to say the tangent inverse of this guy right here is going to give me 60 degrees, okay? So if I subtract 60 degrees away from 180 degrees, okay, because this is my reference angle in quadrant 2, well, it's going to be 120 degrees, okay? So that's my theta. Let's get rid of this. Let's put in 120 degrees and 120 degrees. Okay, so that's pretty quick. All right, so from here, I need to get the 4 fourth roots. So in each case, I'm going to take the 4th root of 16, right? Because again, it's the nth root of r. So n is 4, r is 16. So the 4th root of 16 is 2, right? Because 2 to the 4th power is 16. So I'm going to put 2, 2, 2, and 2, okay? Let's go ahead and set this up in each way. So cosine, 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 and then cosine, okay? So what's going to go here, 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 and here? Remember, when you think about the formula, if you call this alpha, it's equal to, again, you take theta, okay, which in this case is 120 degrees, and you divide it by n. So you divide it by 4. So in this case, that would be 30 degrees, okay? Then plus you have your 360 degrees times your integer k divided by your n. So 360 degrees divided by, in this case, it would be 4, would be 90 degrees, okay? So this would be 90 degrees times k. So for the first instance, this would be 30 degrees. So let's go ahead and put 30 degrees here. I'll fill out the rest in a moment, okay? In the next instance, it's going to be plus 90 degrees. So this would be 120 degrees. Then plus 90 degrees. So this would be 210 degrees. Then plus 90 degrees. So this would be 300 degrees. So let's get rid of this. And let's put our plus, 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 I, and I. And then the sine, the sine, the sine, and then the sine of 30 degrees, close that down, and this will be 120 degrees, close that down, and then 210 degrees, close that down, and then 300 degrees, okay? So these are our 4 fourth roots, okay, for this number in polar form. Okay, so how would we go about graphing these complex roots? Well, basically, each of these can be represented as a position vector in the complex plane. So notice that your magnitude in each case is 2. Okay, so 2, 2, 2, and 2. So what you could do to represent that is you could have a little circle with the center at the origin and where the radius is 2. Okay, so each one of these as a vector is going to have an initial point at the origin and a terminal point that's going to touch that circle that you drew. Okay, and then in terms of the direction angle for the vector, you just get it from here. So the first one would be 30 degrees, the second would be 120 degrees, the third one would be 210 degrees, and the fourth one would be 300 degrees, okay? So these guys are going to be spaced 90 degrees apart, okay? So equally spaced 90 degrees apart. So if we go to our little coordinate plane, and I know that most people put imaginary here, so you can put that if you want. So you can put imaginary, and then for this, you could put real. But again, if you write this as x plus yi, then x could still be your real axis, and y could be your imaginary axis. It's really up to you or your teacher, okay? So I'm just putting it this way. So when we think about this, again, the first solution was 2 times the quantity of the cosine of 30 degrees plus I times the sine of 30 degrees. We abbreviated it here. But you can see that I have a position vector. The initial point is at the origin. The terminal point is going to touch this little circle that I drew, okay, with a radius of 2 and a center at the origin. Okay, so you see that this is a 30-degree angle, okay? And then if we go another 90 degrees here, so this is another 90 degrees, you can see that little 90-degree symbol there. Basically, I'm going to get to my next solution. So the angle here is 120 degrees. Again, if I started here, 30 degrees plus 90 degrees gives me 120 degrees, okay, for the whole thing. And then basically, you can see that it touches, again, our little circle. If we keep going around, this is another 90 degrees, and then this is another 90 degrees. Okay, so it keeps putting you to another solution. So this angle here, if I started here and went all the way to here, this is 210 degrees. If I started here and went all the way around to here, this is going to be 300 degrees. Okay, so that's basically how you can sketch the graph. If you're given this as an assignment, again, just take your magnitude. Okay, in each case, ours was 2, and draw yourself a little circle with the center at the origin and the radius of that number. Okay, in our case, it's 2. Then what you want to do is have position vectors. So they start at the origin, and their terminal point is going to be on that circle, and your direction angle in each case is given by the angle. So here it's 30 degrees, here's 120 degrees, here it's 210 degrees, and here it's 300 degrees. All right, so let's wrap up the lesson and look at another example. Here we're going to be solving a simple equation using the roots of a complex number. Okay, let's say we saw something like x cubed minus 27, and this was equal to 0. The first thing, we know that since this polynomial here is of degree 3, okay, we have this exponent of 3 here and none higher, well, we know we're going to have exactly 3 complex solutions for this equation. Okay, that's the fundamental theorem of algebra. So how could we use the roots of a complex number to solve an equation like this? Well, the first thing is I could add 27 to both sides, okay? And I could set this up and say, really, this is x cubed is equal to 27. Okay, let's pause and think about this for a minute. I am looking for a value that I can plug in here and cube it and get 27. So in other words, what number cubed gives me 27? So if I found the 3 complex cube roots of 27, I could plug them in for x, and I would have a true statement, okay? So you might be thinking, well, 27 is a real number. Remember, all real numbers are complex numbers. The real number system is a subset of the complex number system. I can write 27 as 27 plus 0i, okay? So with this format here, I can also write this in polar form. This is really easy to do. If you think about the r value, it's just going to be 27, okay? Because you think about this as, okay, well, r is equal to the square root of 27 squared plus 0 squared. 0 squared, you can just get rid of that, okay? And the square root of 27 squared is just 27. So our r value is 27. Then, in terms of this inside part, it's easy as well. So you'd have the cosine of, again, theta plus I times the sine of theta. So you don't need to do any inverse tangent function here or anything like that. Just think about this complex number if you graphed it on the complex plane. You would simply start at the origin and go 27 units to the right, okay? So there's no movement at all vertically, right? You're on the x-axis or the real axis if you want to think about it that way. So really, this is going to be a 0-degree angle, right? I haven't moved off the real axis. So I'll just go ahead and put this as a 0-degree angle. Okay, and that's all it is. So this is me writing the number 27, first in rectangular form, and then in polar form. Now, in order to find my 3 complex cube roots, I'm going to start with my simple little formula. So I have the nth root of r. So in this case, n is 3, right, because I'm looking for a cube root, and r is 27. Well, the cube root of 27 is 3, right? 3 times 3 is 9, 9 times 3 is 27. Okay, so I can set this up. I know I have 3 of them, so I'll go 3, I'll go 3, and I'll go 3, okay? Let me just write all this out. So we have cosine, cosine, and cosine, and we're going to use alpha, we're going to use alpha, and alpha, and I'll replace this in a moment. So plus, plus, and plus, I, and then sine, sine, and sine, okay? And I'm going to use alpha again, and alpha again, okay? So again, these are all going to change based on that input for k. So to find alpha, let's go ahead and set this up over here, put a little border here. To find alpha, The idea is that it's theta, whatever this is, in this case it's 0 degrees, divided by n, which in this case is 3, okay? So 0 degrees divided by 3 is just 0 degrees. So this is 0 degrees. You can put it there or leave it off. It doesn't matter. It's not going to change anything. I'm just going to leave it for the sake of completeness. So then plus you have 360 degrees divided by n. In this case, that's 3. So this is 120 degrees, okay? And then times your k. Now, k is going to be 0, 1, and 2. Basically, your pattern is what? It's 0, 1, 2, 3, n minus 1. Let me put a comma in there to make that complete. And basically, you have 3, so 3 minus 1 is 2. So in this case, we would only go up to 2. Okay, so that's how that works. So I'd start with a 0 there, and of course, 0 degrees plus 0 degrees is just 0 degrees. So the first guy here is just going to be 0 degrees. So I can put that in here, and that should make sense. If I cubed this, 3 cubed would be 27, and then you would basically have 3 times 0 degrees, which is still 0 degrees, and 3 times 0 degrees, which is still 0 degrees. So in polar form, I would be right back to this here. 27 times the quantity, cosine of 0 degrees, plus I times the sine of 0 degrees, which again in rectangular form is this, and written just as a real number is this, okay? So then the other one, I'm just going to add 120 degrees each time. If I plugged in a 1 there, this would just be 120 degrees. So 120 degrees, 120 degrees. Add another 120 degrees. If I plugged in a 2 there, this would be 240 degrees. So 240 degrees and 240 degrees, okay? So these three numbers here in polar form, these three complex numbers in polar form, if you cube them, they would each give you 27. Now, typically, if you were in an algebra class, you would not give this as your solutions, right? You would want to convert this back into rectangular form, okay? So how would we do this? The cosine of 0 degrees is going to be 1, and the sine of 0 degrees is going to be 0. So basically, you would have 3 times 1, which is 3. So I would say x is equal to 3. Okay, that would be my first solution. For this one, the cosine of 120 degrees and the sine of 120 degrees, let's think about this. There's a 60-degree reference angle here, 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 and here, right? 120 degrees, 240 degrees, you have a 60-degree reference angle. So the cosine of 60 degrees is going to be 1/2. And the sine of 60 degrees is square root of 3 over 2, okay? So it's just a matter of getting the signs right. Remember, sine is going to be positive in quadrants 1 and 2, and 120 degrees is in quadrant 2. Cosine is going to be positive in quadrants 1 and 4, okay? So basically, cosine is negative in each case, because this is quadrant 2, this is quadrant 3, and sine is positive here and negative here, okay? So to get my solutions, let me write this out. I'm just going to scroll down a little bit so we have some room. For this one, I would have what? 3 times, this would be the quantity, negative 1/2, plus this guy is going to be square root of 3 over 2, okay, times I. So if I go ahead and distribute the 3 into each term, I would have negative 3/2, and then plus my 3 times square root of 3 over 2 times I. Okay, so that's another solution. Then the other one, let me just go ahead and keep this as negative, and I'm going to change this to negative now. So basically, you would have negative 3/2 again, and then minus the 3 times square root of 3 over 2, and then times I, okay? So I would write this in a more compact form. I would just do plus or minus here and get rid of this. That way you can more cleanly write your 3 solutions. So if you were in an algebra class and they gave you this equation, you would want to give this as a solution. Now, in this particular case, this is probably not the fastest method to do this, but it's one such method that you can get a solution. Now, let's think about this graphically. If I wanted to show these solutions, again, I'm going to do this in polar form, okay? So on the Argand diagram or the complex plane, again, the magnitude is 3 in each case. So that's the length of your vector. So if you're making a circle, okay, with a radius of 3 that is centered at the origin, each one of these vectors is going to touch that circle, okay? That's going to be your terminal point that lies there, okay? And then your direction angle for your vector is going to be 0 degrees, then the other one's going to be 120 degrees, then the other one's going to be 240 degrees, okay? All of them are position vectors, so they start, or their initial point is at the origin. So graphically, this is a rough sketch of this guy. Again, I have a little circle that's drawn, and the radius is 3, and the center is at the origin, okay? Then you have your 3 position vectors. Notice that they're all going to have an initial point at the origin. The terminal point in each case is on that circle, again, where the radius is 3 and the center is at the origin. So your first angle is 0 degrees, okay? It's given by this 3 cis 0 degrees. Again, this is the abbreviation. The second angle is 120 degrees, okay? So we come from here, we rotate 120 degrees, and now we have that vector there, okay? And the terminal point's there. And then the last one, if I rotate around here, this is going to be a 240 degree angle, okay? So that's how you would sketch the graph of this guy. You'll notice that these guys are equally spaced 120 degrees apart, right? 120 degrees, this is 120 degrees, and this is 120 degrees as well. So this is how you can graph your solutions if you're asked to do them. Again, figure out the magnitude or the length of the vectors. You're going to sketch yourself a little circle, okay, with a radius of that number. In this case, it's 3, and a center at the origin. So all of your vectors are going to be position vectors, initial point at the origin, terminal point's going to be on that circle, and you just get your direction angle from your roots. So we had 0 degrees, 120 degrees, and then 240 degrees. In this lesson, we want to talk about polar coordinates. All right, so up to this point, we've exclusively used something called the rectangular coordinate system, or some people refer to this as the Cartesian coordinate system after the inventor. And we've worked with this guy to plot these points, or you could say ordered pairs, and also to graph equations. So I want you to recall that the rectangular coordinate system is going to feature the x-axis, which is horizontal, and the y-axis, which is vertical. Okay, the meeting point between the two is going to be right here, and this is referred to as the origin. Okay, so this is your origin, okay? And when we specify this using an ordered pair, remember this is the x value, comma, the y value. So for the origin, it's going to be 0, 0, okay, because the x value is 0 and the y value is 0. Now, if I think about another point, let's just do a few. So let's say we do something like 6, 7. Let's say we do -6, 7. Let's say we do -6, -7. And let's say we do 6, -7, okay? So these are directed distances, okay, from the origin. So in other words, the first guy here, okay, or the first component, as they say, the x value tells you how to move horizontally. Okay, if it's positive, I'm moving to the right. If it's negative, I'm moving to the left. So for this guy, 6, 7, I'm moving to the right by 6 units. Okay, so let me just circle this temporarily. And then the second guy there, the y coordinate, is telling me how much to move vertically, right? So if it's positive, I'm going up. If it's negative, I'm going down. So let me go ahead and from the origin go up by 7 units, okay? So you basically want the meeting point between the two. So you can go 6 units to the right and 7 units up, or you can go 7 units up and 6 units to the right, okay? Either way, you're going to end up at this point right here. This is going to be your 6, 7. And I know most of you know how to do this already, but basically we just want to recap this before we get into the polar coordinate system. Now for the next one, we have -6, 7. So that means I'm going 6 units to the left, right, because it's -6. And then I'm going 7 units up because it's +7, okay? So 6 units to the left, 7 units up. So this is my -6, 7, okay? The other one is -6, -7. So both are negative. So it means I'm going to the left, okay, because it's a -6, and I'm going down because it's a -7. So 6 units to the left and 7 units down. That's going to put me right there, okay? So this would be -6, -7. And then lastly, we have 6, -7. So this is positive for x and y is negative. So it means I'm going to the right and I'm going down, right? So 6 units to the right and 7 units down. That's going to put me right there. Okay, so this is 6, -7. All right, now let's think a little bit about something called the polar coordinate system. And to start this out, I'm just going to show you how we get the polar coordinates. So let's say I had something like the point where we have 5, 6. So this is as an ordered pair. Again, this is x, y. So starting at the origin, I know that to get to this point, I could go 5 units to the right and 6 units up. So that puts me right there. Or alternatively, I could start at the origin and go 6 units up and 5 units to the right. So basically that gives me the directed distances from the origin. We know that. But we also want to be able to write this with polar coordinates, which is going to be an r value, comma, a theta value. Okay, so where does this come from? Well, essentially what we can do is we can create a little position vector. Okay, so the initial point is at the origin. The terminal point is going to be at that point here, okay, with our 5, 6. So what I could say here is that with rectangular coordinates, you have x, y. In this case, it's 5, 6. So hey, start at the origin, go 5 units to the right and 6 units up. With polar coordinates, it's going to be r, theta, okay, where r is the distance from here to here. Okay, if you're thinking about this as a vector, remember the length of the vector is called the magnitude of the vector. So in this case, that's going to be your r, right? So this is the square root of 61. And then the Theta here is the directed angle. So in other words, how much do I need to rotate counterclockwise? So starting from the positive x-axis, if I'm facing this way, I need to rotate by 50.19 degrees to get to this position vector. Okay, so let's say this is 50.19 degrees. This is an approximation, and I'll talk about how to get this in a moment. But essentially, I want you to see that it's just two ways to get to the same point, right? I could say, hey, start at the origin, go 5 units to the right and 6 units up. Or I can say, hey, start at the origin, okay, facing the positive x-axis, rotate 50.19 degrees, and then walk forward by the square root of 61 units, okay? So two ways to kind of do the same thing. Now, if we want to talk a little bit about where this r value came from and where the theta value came from, see here how I made a little right triangle, okay? And essentially we see that the length of this vertical leg here is given by the y value of 6, right? So this is basically from 0 to 6, so this is given by 6. The length of this horizontal leg here is given by the x value of 5. Okay, so really easy to work with this. You just use the Pythagorean theorem. So if you want your distance from here to here, or the magnitude of the position vector, the distance squared would be equal to, you would have 5 squared and then plus 6 squared. So d, your distance between these 2 points, would be equal to the square root of 5 squared is 25, plus 6 squared is 36. If you sum those two together, you're going to get 61. Okay, so the distance between these 2 points, or your r value, is the square root of 61. Okay, so that's where that came from. In terms of theta, okay, calculating that, basically for most textbooks, they're going to use the inverse tangent function. Remember, the tangent of some angle theta is y over x, okay? So in this case, your y value is 6, your x value is 5. So let's go ahead and say that the tangent of theta is 6 over 5, okay? And then because we're in quadrant 1 here, we can go ahead and just strictly use the inverse tangent function, right? So I can just say the tangent inverse of 6/5 like this is going to give me, and this is an approximation, so we'll say approximately 50.19 degrees, okay? Now, if you're in another quadrant, you have to be really careful because remember, the inverse tangent function is only going to give you something in quadrant 1, okay, if this argument is positive, or in quadrant 4, rotating clockwise, if this argument is negative. So be really, really careful. We're going to work a lot of examples today, and I'll show you how to deal with that. All right, now what I want to do is just take you through the basics of the polar coordinate system. So with the polar coordinate system, everything is going to be based on a fixed point, which is called the pole or the origin, okay? And essentially, most books are going to name this with a capital letter O. So this is our pole, okay, to get things started. From there, you're going to create an initial ray, which is called the polar axis. So that's going to be this guy right here. Okay, so that's your initial ray called the polar axis. And generally speaking, this is drawn in the direction of the positive x-axis. Now, once we have this set up, we can find a point P in the plane using the coordinates r comma theta. Okay, so we have our pole here. Okay, that's set up. We've constructed the polar axis. So now if I give you r comma theta, I can locate any point P, okay? So r is the distance from the pole O, okay, to that point P. Okay, so basically if you think about this as the vector OP, what is the magnitude of that vector? Okay, that's going to be r. And then if I think about my directed angle theta, well, this is just telling me how much do I need to rotate counterclockwise from the polar axis to get to this vector OP. All right, so what I want to do now is talk a little bit about how to convert between the polar coordinates and the rectangular coordinates. So what we did here is we just took the drawing from the last section, okay, and we just put it on top of basically a coordinate plane that we're used to, right? So the rectangular coordinate plane, you'll see that we have the pole that's going to be fixed at the origin of the Cartesian coordinate plane. And basically the polar axis is drawn to coincide with the positive x-axis, okay? So once we do this, we can obtain a few insights here, okay? So we have this point P in our plane, which can be assigned the rectangular coordinates x comma y, or the polar coordinates r comma theta. So let's say I gave you r comma theta, and I said, hey, I want you to give me x comma y. How could you do that? Well, if you consider that the cosine of theta is equal to what? Remember, I've formed a little right triangle here. So essentially, I can say that it's going to be the adjacent, which is going to be x here, okay, over the hypotenuse, which is going to be r here. Okay, so x over r. And then if I think about the sine of theta, it's the opposite, which is y, over the hypotenuse, which is r. So the sine of theta is y over r. And I didn't make that equal sign very good, okay? In each case, I can multiply both sides by r. I can solve for x or y, okay? So I can say that x is equal to r times cosine of theta. So x is equal to r times cosine of theta. Okay, so that's all you need to do to find x. And then for y, it's going to be r times sine of theta. Okay, so y is going to be r times the sine of theta. Okay, so pretty easy to go from polar coordinates to rectangular coordinates. Now, let's erase this and let's consider the other one, which is a little bit more involved. But basically, if I start with my rectangular coordinates, my x comma y, and I want to go to my polar coordinates r comma theta, let's think about that. So essentially what I'm doing here is I'm, again, returning to the fact that for r, I want the distance from here to here, okay? So if I'm given the x comma y, again, I'm just using the Pythagorean theorem. R squared is going to be equal to x squared plus y squared. So r is going to be equal to the square root of x squared plus y squared. Okay, that's all it is. So very easy to remember this. Now, the tricky one is to get theta, right? Because you have all these different scenarios you have to consider. If you're in quadrant 1, you can just use your inverse tangent function, right? Because the tangent of theta is what? It's going to be y over x. We know this already. But if I'm not in quadrant 1, then basically I need to get a reference angle, okay, using the inverse tangent function. And then from there, I need to take the appropriate action based on what quadrant I'm in, right? So if I'm in quadrant 2, 3, or 4, okay? So let's go ahead and think about a simple little example. And so what I have here is the negative of 3 times square root of 2 over 2, and then comma, the negative of 3 times square root of 2 over 2. Okay, so these are rectangular coordinates. I want to go to polar coordinates, and then I'm going to show you how to plot this on the polar grid. Okay, so essentially, this is again my x value, and this is my y value. Okay, so what did I just say? Essentially, if I want to find the r value is going to be the square root of x squared plus y squared. Okay, so that's the first thing I would do. So all I need to do, let's go the square root of, I'll put r out here, is equal to, I'll have the negative of 3 times the square root of 2 over 2, and this is going to be squared. And then plus, I've got to do this again, so the negative of 3 times square root of 2 over 2, and this is going to be squared. Let me make this a little bit longer so it's proper. And so if I think about this, I know that negative in each case is going to be gone, right? Square and negative, you get a positive. 3 squared is 9. The square root of 2 squared is 2. And then 2 squared is 4, okay? So essentially what I'm going to end up with is canceling this with this and getting a 2, okay? So you'll end up with 9 halves. So I'll have 9 halves here and 9 halves here. So basically I would have r is equal to square root of 9 halves plus 9 halves. You have a common denominator there. So basically 9 plus 9 is 18. You would have 18 divided by 2, which is going to be 9. Okay, so r is equal to the square root of 9, which we know is 3. Okay, so let me erase this from over here. Let me put this as r is equal to 3. Now, when we think about the directed angle theta, okay, this is where it gets a little bit tricky. First off, consider that your x-coordinate is negative and your y-coordinate is negative. So if you think about this on your rectangular coordinate plane, if your x value is negative and your y value is negative, you're going to the left and you're going down. So that means that theta is in quadrant number 3, okay? So let's keep that in mind. So let's do our inverse tangent function. If you have the same thing over itself, okay, and it's not 0, you're going to get 1. So basically I want the tangent inverse of 1. Type that into your calculator, and you're going to get 45 degrees. So if I'm in quadrant 3, what I want to do is I want to take 180 degrees, and I want to add my reference angle there of 45 degrees, and this is going to give me 225 degrees. Okay, so this is 225 degrees. So let's erase this. So I'll just put that these are polar. So the polar coordinates, okay, like this, would be, you would have 3 for your r value, and then your theta value would be 225 degrees. So to plot this guy, this is going to be 3, 225 degrees. On our polar grid, basically what we do, to construct this grid, remember you have your pole or your origin. Okay, let me make that visible. And essentially, this is going to be the center for everything, okay? Then you're going to have your polar axis, which again is drawn in the direction of the positive x-axis. So you have some notches here. So this is 1, this is 2, 3, 4, so on and so forth. And basically what these are going to give you, you're going to make some circles, and the first one is going to have a radius of 1, right? So basically up here, this is 1. This would be -1 if you think about it as the regular Cartesian coordinate system, and this would be -1, right? But the distance from the center, or the pole, to any one of those points would be 1, right? So that circle would have a radius of 1. Then you would have a circle with a radius of 2, then 3, then 4, then 5, so on and so forth. Then you also have these angles here, which are in increments of 15 degrees, or if you're working with radians, pi over 12 radians, okay? So essentially, if I want this 3, 225 degrees, I'm finding the meeting point of a circle with a radius of 3, okay, and an angle of 225 degrees. So I can come out to this circle with a radius of 3, and then I can swing around, okay, to this angle that's 225 degrees. So that's going to put me right here. Okay, so this would be the point on this polar grid where we have 3 as the radius and 225 degrees as the directed angle. Okay, now there's obviously other ways that you could name this point. I'm going to get to this later on. Okay, you realize that you could swing around again 360 degrees, or you could actually rotate clockwise 360 degrees, or multiples of that. Okay, so we'll talk about that later on. All right, let's take a look at another example. So here we're given the rectangular coordinates. We have the negative of 2 times square root of 3, comma 2. So again, this is your x value, and this is your y value. So to get the r value, what are we going to do? Remember, this is equal to the square root of, you take the x value squared, so the negative of 2 times square root of 3, okay, being squared, and then plus, you're going to go ahead and take the y value squared. So 2 squared, let's just go ahead and write 4, okay? So if I square negative 2, I get 4. If I square the square root of 3, I get 3, okay? So this would be 4 times 3, which is 12. So let me go ahead and put a 12 in there. And 12 plus 4 is obviously 16, and the square root of 16 is going to be 4. Okay, so we have the r value. Again, that's pretty easy to get. When you consider theta, okay, you have to think about what quadrant you're in. So if my x value is negative and my y value is positive, that means I'm going to the left and I'm going up, right? So I'm going to be in quadrant 2. So theta is in quadrant 2. Okay, so always figure that out first. So then what I want to do is I want to think about, okay, well, the tangent of theta is equal to y, which is 2, over x, which is negative 2 times square root of 3. Let's go ahead and cancel this with this. And basically I have 1 over, you would have the negative of the square root of 3. Let's put the negative out in front, and then we'll put the square root of 3 over here. And then I'm going to rationalize the denominator, so square root of 3 over square root of 3. So this becomes the negative of the square root of 3 over 3. Now, I'm not going to use the negative because I want something in quadrant 1 when I use my inverse tangent function. So let me erase all of this, okay? And basically what I'm going to do is I'm going to say I want the inverse tangent of, let me go ahead and make this positive, so I'll say the square root of 3 over 3. If I punch that into my calculator, I'm going to get 30 degrees, okay? So the way this works, if I'm in quadrant 2, okay, and I want an angle with a reference angle of 30 degrees, I want to take 180 degrees and subtract 30 degrees away from that. So basically, my theta would be equal to 180 degrees minus 30 degrees, which is 150 degrees. Okay, so 150 degrees. And I forgot to put my 0 there, so let me put that in. So the polar coordinates are let me write this out. The polar coordinates would be what? It's your r value, comma, your theta value. So 4, comma, 150 degrees. So to plot this, so again, the point would be 4, comma, 150 degrees as polar coordinates. And again, all I'm going to do is I'm going to go out to a circle with a radius of 4, okay? And what I'm going to do from there is just swing around, okay, until I get to 150 degrees. Let's go ahead and plot that point right there, okay? So this is going to be 4, comma, 150 degrees. Again, plotting this on the polar grid. All right, let's take a look at an example where we have polar coordinates and we want to convert to rectangular coordinates. So first off, we have 6, comma, 75 degrees. Let's just plot this real quick. So again, what I want to do, I want to go out to a circle with a radius of 6. Okay, so right here. And then I'm going to swing around to an angle that's 75 degrees. So that's going to put me right there. Okay, so that's going to be my point 6, comma, 75 degrees. All right, so let's consider how to transform this into rectangular coordinates now. So remember, if we want to write this as x, comma, y, the relationship we talked about earlier is that x is equal to r times cosine of theta, and that y is equal to r times the sine of theta. So these are two things you need to memorize. You're going to use it basically all the time. Now, once we think about this, we have our r value of 6, so you might as well just put this as 6 in each case. Okay, so 6 and then 6. And then what is the cosine of 75 degrees and what is the sine of 75 degrees? So remember, this is not on your unit circle, okay? So what you can do is use identities, okay? We talked about this earlier in the course, to get an exact value, okay? If you punch it into your calculator, you get an approximation. So you could write 75 degrees as 45 degrees plus 30 degrees, okay? And you could use your cosine sum identity or your sine sum identity, depending on what you're working with, to get the exact value, okay? I'm just going to give this to you because we don't want to spend time working on something we already did. So essentially, the cosine of 75 degrees, I'm going to put some parentheses here, and I'll put it as the square root of 6 minus the square root of 2, and this is going to be over 4, okay? And then the sine of 75 degrees, again, I'm going to put, let me kind of slide this down a little bit so it's not in the way. I'm going to put this as, we'll have the square root of 6 plus the square root of 2, and this is going to be over 4, okay? So this is getting exact values. If you want to punch it in your calculator and approximate it, you can do that too. It's up to you. So let's go ahead and cancel this with this, okay? So this would basically be a 3, and this would be a 2. Okay, and then from there, I would distribute this in. So I would have 3 times square root of 6. So 3 times square root of 6 minus 3 times square root of 2, and this is over 2. Okay, so this is going to be your x coordinate. Then here, this cancels with this. Again, this is the 3, and this is a 2. And then you're going to distribute that 3 into each. Okay, so let me put this as a 2. This would be a 3, and this would be a 3. Let me slide this down. So this would be 3 times square root of 2. Okay, so if you want to write this as rectangular coordinates, you can go ahead and say that it would be 3 times square root of 6 minus 3 times square root of 2 over 2, and then comma. Let me erase this. This is all going to not fit. So let me slide this down a little bit so it all fits on the screen. And then over here, I'd have 3 times square root of 6 plus 3 times square root of 2, and then over 2. So kind of messy, kind of nasty. Again, your teacher might allow you to approximate it, so it might be a little bit quicker for you to do it that way. All right, let's look at one more example where we're going from the polar coordinates to the rectangular coordinates. So here we have negative 4, 120 degrees. So the r value, okay, is going to be negative 4, and the theta is going to be 120 degrees. So let's pause for a minute. When you get an r value that's negative and you're asked to plot this guy, it can be a little bit confusing, okay? When you get a theta value that's negative, that's pretty simple. We know that a negative angle just means I'm rotating clockwise, right? So let's deal with this r value that's negative first. Let's go to the polar grid, and let's first graph positive 4, 120 degrees, and then we'll think about what negative 4, 120 degrees would mean, okay? So if I step out to a circle here with a radius of 4, so let me go out here, and let me swing around, okay? And I'm just going to draw a little terminal ray. I'll do that the best that I can. I'm not a good drawer. But basically, that point's going to be right there, okay? So you'll notice that that point is on that terminal ray, okay? So this is going to be the 4, 120 degrees, okay? We know how to find that at this point. Okay. Now, if I wanted to find negative 4, 120 degrees, all it means is that I'm basically going to reflect this point across this pole. Okay, so here's the pole right here, and if I reflect it across the pole, I'm basically going to go in the opposite direction. So I'm going to go this way 1, 2, 3, 4 units. So that's going to be right there. Okay, you can think about making a terminal ray here, and think about having the angle. Let's say I had the angle. I just start here and go all the way around. That would basically be a 300-degree angle. Okay, so negative 4, 120 degrees would represent the same point as 4, 300 degrees. And we're going to talk more about these different forms in a moment, okay? But for right now, you could see a few different ways that you could go about finding this. So let me go to a fresh sheet here where this is already plotted. So the first thing, I'm going to label this as negative 4, comma, I'm going to do 120 degrees, okay? I could have found this by going to 120 degrees like this, and then basically just instead of going forwards, I would just go backwards by 4 units. Okay, that's probably the easiest explanation. So I would just say, okay, I'm here, so I'm going to go 1, I'm going to go 2, I'm going to go 3, I'm going to go 4. So out to a circle that has a radius of 4, right? I'm just turning around and going backwards. That's what the negative 4 is basically telling me, okay? So that would be one way I could get to my point. Another way, and this might be helpful for you, you might want to plot 4, 120 degrees. So I got to 4 here, swing out to 120 degrees. So I'm going to be right there. So this is my 4, 120 degrees. And notice that if I wanted to swing over here, okay, I'm basically going to add 180 degrees to this angle. Okay, or I could subtract 180 degrees from the angle as well if I wanted to. So I could either say that this is going to be plus 180 degrees, which would be 300 degrees, or I could subtract away 180 degrees and say this is negative 60 degrees if I wanted to rotate clockwise, okay? But essentially, those are the ways that you could think about doing this. Once you graph these a few times, it becomes a little bit easier to work with in your mind. But just know if you have a negative r value, you're basically going to walk backwards, okay? That's what it means. So let's go back and let's think about putting this into rectangular form, okay? So we know again that our x value is equal to, we would have the r value, which is negative 4, times the cosine of 120 degrees, and the y value is negative 4, times the sine of 120 degrees, okay? So we know that 120 degrees is going to be in quadrant 2. It's got a 60-degree reference angle. And the cosine of 60 degrees is going to be a half, okay? But cosine is negative, okay, in quadrant 2, so this would be negative 1/2. So times negative 1/2, so of course this would be positive 2. So the x value is positive 2, very easy to find. The sine of 120 degrees, again, a 60-degree reference angle. Sine is positive in quadrant 2, so the sine of 60 degrees is square root of 3 over 2. So this is going to be times the square root of 3 over 2. I can cancel this with this, and I would have the negative of 2 times square root of 3. So negative 2 times square root of 3. So then my rectangular coordinates would be 2, negative 2 times square root of 3. Okay? So basically, I want to go from here into our next point, which is talking about alternative forms for coordinates of a point in polar form. So for a given point in the rectangular coordinate plane, you're going to have an infinite number of pairs of polar coordinates. So sometimes your teacher will say, give me, 4 examples of other polar coordinates that are the same as this polar coordinate I'm giving you. Sometimes they want a general formula. So I'm just going to give you the general formula here, and then you can apply that based on the example you get, okay? So the first one is pretty easy to understand. If we have some r comma theta, this is the same as if I said r comma, and then your theta plus 360 times n degrees, n is just any integer, or theta minus 360 times n degrees. Now, the plus or minus here is given in some books. You really don't need it. You could just put plus because n is any integer, so you can make it positive, you can make it negative, you can do whatever you want, okay? But some books will put plus or minus, others will just put plus. If you go back to, let's say, this guy right here, where we have 4, 120 degrees, well, if you think about it, I could add 360 degrees to this, and I could say, well, also the same point could be located if I said 4, this would be 480 degrees, right? Because basically from here, I would swing around another 360 degrees and be right back to that same point. I could add 360 degrees again and get to 840 degrees. Then I could do it again and again and again. And the same thing is true if I subtracted 360 degrees away from 120 degrees. So some other coordinates would be something like 4, negative 240 degrees. Okay, so that would all locate the same point. Okay, so now let's look at this second formula. This one is a little bit more challenging to understand. But remember, if you have r and you have the negative of r, remember when you think about the negative of r, you're basically going to be walking backwards. Okay, so this is what this is related to. So again, you have this theta, whatever your angle is, plus or minus, you're going to have this 180 degrees times this quantity. So let me distribute this out. So I'm going to put plus or minus, and I'll go ahead and say you'll have your 180 degrees times 2n. So let's say this is, we'll say 360, we'll say n degrees. And then I'll say plus, I'll go ahead and say do my 180 degrees like this, okay? So you could have positive or you could have negative. You're going to see that you can actually drop the plus or minus here as well. I'll go through some examples and prove that to you. Most books will just write this with a plus sign, but others put plus or minus, okay? So it's right either way. So if we go back and we think about alternative ways to locate this point. Remember, this was negative 4, 120 degrees, okay? So all we're saying is that we could have done the negative of this number, so that's 4, and then I could add or subtract 180 degrees to this. So if I add 180 degrees, I would be at 300 degrees, okay? So in other words, I could have gone out to right here, and then I could have swung by 180 degrees this way, right, to get to 4, 300 degrees, or I could have started there, and I could have swung 180 degrees this way. This would be clockwise, so that would be me subtracting 180 degrees. So I could have also said this is 4 comma. If I subtract 180 degrees from this, I would get negative 60 degrees. Now, once I've added or subtracted the 180 degrees, I could then swing by multiples of 360 degrees, right? Either positive or negative. So that's where these formulas are coming from, because from here I could say, okay, well, this is 4 comma, 300 degrees plus 360 degrees would be 660 degrees. Okay, so that's another way to locate that point. So in other words, I could have started here, and I could have swung around 180 degrees, okay, and then swung around another 360 degrees to get to that same point, okay. Also, what I could have done, I could have started at 4 comma negative 60, and I could subtract away another 360 degrees, which would be negative 420 degrees. Again, another way to locate the same point. So there's a lot of different ways you could have done this. So again, we put this into this nice little convenient formula, okay? So basically it relies on the fact that you're first adding 180 degrees, and then from there you could add 360 degrees, and then times some integer n. That could be positive, it could be negative, it could be whatever. Again, you see this plus or minus here, but you could drop that and just put a plus, and I'll show you that in the example. All right, so let's just look at an example here. So we have the polar coordinates 3 comma 240 degrees, and what I'm going to do is ask you for a formula for all the pairs of polar coordinates that describe the same point. Again, your example might be different. They might say find them within this certain range. You just have to apply it to that, okay? So what I'm going to do here is first start by saying, okay, the 3 would be the same. And what I would do here is I would add 360 times n to this, right? So the formula you saw was theta plus or minus 360, and you would do n degrees, okay, like this. Well, theta is 240 degrees, so let me put that in there. So 240 degrees, and then plus or minus your 360 times n. Well, I don't need the plus or minus because I can get anywhere I want to go by just varying n, right? N is any integer, so it could be positive, it could be negative. So again, you can put plus or minus, it's not wrong, but really most books will just put plus. You don't need the minus. So let's go ahead and get rid of that. Okay, so the next one is a little bit more challenging to understand. So remember, you would put the negative of whatever this number is. So in this case, it's 3. So I'm going to go ahead and put negative 3. And then I'm going to put a comma. And let me go through and work out the two different scenarios. So I'm going to go ahead and say I have 240 degrees. Okay. Then I'm going to go plus. Remember, you're going to have your 180 degrees. And then you're going to have plus your 360, okay, n degrees. So this is basically where I'm swinging 180 degrees, and then from there I can add multiples of 360 degrees. I'm also going to do this with the minus sign to show you it comes out the same. So let me close this real quick. Negative 3 comma, I would do 240 degrees, and then minus 180 degrees, and then minus 360 n degrees, okay? So basically, for this one, 240 degrees minus 180 degrees would be 60 degrees. Okay, so this would be 60 degrees. And then let me just tighten this down a little bit. We're going to end up erasing this one, so it doesn't really matter. Then this one, 240 degrees plus 180 degrees is 420 degrees. Okay, so 420 degrees. And if you think about it, 420 degrees, if I subtract off 360 degrees, this is going to be coterminal with 60 degrees. So really, I could just put this as 60 degrees, okay, and just slide this down. And now we want to think about this. Do I need the plus or minus here? No, because I can get wherever I want to go by just plugging in different integers for n, right? If I want to do negative, if I want to do positive, I'm allowed to plug in whatever I want there as long as it's an integer. So I can go ahead and get rid of this, okay, and just list it with the plus sign. Again, if you want to put plus or minus, it's not wrong, but it's just overkill, right? So I'm going to list this as my answer. So 3 comma 240 degrees plus 360 n degrees. And negative 3 comma 60 degrees plus 360 n degrees. In this lesson, we want to find the distance between polar points. All right, so let's say that I asked you to find the distance between this 4 comma 105 degrees and 3 comma 225 degrees. How could we do this? We know that if we have the rectangular coordinates, right, and we're working on the rectangular coordinate plane, we can just use our distance formula, right? So if I have 2 points, let's say x sub 1 comma y sub 1, and let's say another one is x sub 2 comma y sub 2. Again, it doesn't matter which point you label as which. I can plug into my distance formula. Let's say d, the distance between the 2 points, is the square root of, I'm going to say x sub 2 minus x sub 1 quantity squared, plus we have this y sub 2 minus y sub 1 quantity squared. Okay, so this works for rectangular coordinates, but I have polar coordinates, okay? So what you could do, and I don't advise you to do this, you could go x is equal to r times cosine of theta, okay? And then y is equal to r times the sine of theta. So you could use that to convert these guys over, okay? Then you could plug in and you'd have your answer. But there's an easier way, okay? We can derive ourselves a little distance formula when we have these polar coordinates. So we could plug into this generically, change up a little bit of notation, and come up with a formula that way. I'll do that at the end of the lesson because I think it's a bit boring. I want to show you this using the law of cosines. I think it's a little bit easier to follow, okay? So let me erase this real quick and erase this. And let's just start by plotting these two on the polar grid, okay? So we'll come down here, and first I'll plot this 4, 105 degrees. So you're going to step out 1, 2, 3, 4 units, okay? So we're going to swing around to 105 degrees. So this is 4, 105 degrees, okay? Then for the other one, we have the 3, 225 degrees. So I'm going to step out 1, 2, 3 units. And again, I'm just going to swing around here to 225 degrees. And I know this is upside down, but you can still read it. So this is 3, 225 degrees like this, okay? So we've plotted those two guys. So now I want to think about, okay, if I had a little line segment that was drawn connecting those 2 points, I want the length of that line segment, which is the distance between those two, okay? So the first thing we need is to figure out what is the angle between the two, okay? So in other words, what is this angle right here? Okay, if I was to sketch this, what is that? Well, again, if you think about the whole part here, let's say I start from here and I go all the way out here, that's a 225 degree angle, okay? But this angle here is only 105 degrees, okay, right there. So if I consider the fact that to go all the way around is 225 degrees, if I wanted to take this part out, okay, I would be excluding this from here, and I should probably do that in a different color. So if I took this part right here out, I would have the angle that I'm looking for. Okay, so basically you're going to do this with subtraction. You can take the larger angle here, which is 225 degrees, and I could subtract away this smaller angle here, which is 105 degrees, okay? And this would give me 120 degrees. So that's going to be my angle between these two guys. You can see I've already made a little diagram for us with this. So again, this is just the angle between the two. Okay, so we need this. Now, we can set up a little triangle once we know this. We already know that if we had a little line segment drawn from here to here, that the length of it would be 4, right? Because this guy is lying on a circle with a radius of 4. This guy right here is lying on a circle with a radius of 3. Okay, so this would be of length 3. So we have a side of 3, an angle of 120 degrees, and a side of 4. We have the side angle side, which allows us to use the law of cosines to find the missing side. So let's just call this A. Again, you can call it whatever you want. You can do A, B, or C. Just going to call it lowercase a, okay? So let's come down here, and let's remember that let's say you were trying to find this lowercase a being squared, so side A. This is equal to, remember, you're going to think about the B and the C that you know. So we're going to say B squared plus C squared, then minus 2 times, you're going to have the B times the C, okay? And then we're going to multiply this by the cosine, okay, of the angle you know. So it's always going to be opposite of this guy. So in this case, it's going to be the cosine of capital letter A, okay? In this case, it's going to be our 120 degrees, okay? So now all you have to do in this case is just plug in. I'm going to say that A squared, so A squared is equal to, one of the sides is going to be 4, the other's 3. It does not matter how you put it in there, and I'll show you that later on. But basically, let's just go ahead and say we have 4 squared plus 3 squared, okay? And I'll put minus, I'll go 2 times, I'll go ahead and say 4, and then times 3, and then times the cosine of 120 degrees, okay? So once you get it to this point, you're just simplifying. You can replace A with D, okay? Because you're trying to find the distance between the two. Doesn't matter, it's just a letter. So I'll say that basically my D squared is equal to 4 squared is 16, then plus 3 squared is 9, then minus, you're going to have 2 times 4, which is 8, times 3, which is 24, and then multiplied by the cosine of 120 degrees. Again, that's going to be in quadrant 2. You have a 60-degree reference angle. So cosine of 60 degrees is a half, so cosine of 120 degrees would be negative 1/2, okay? So to simplify this, 16 plus 9 is 25. Let's just do it right here. We'll say this is 25. And then this would cancel with this. The negatives would also cancel, so this is going to be plus. And basically 24 divided by 2 is 12. So I'll say this is 25 plus 12, okay? Which is basically going to give me 37. So we have that the distance squared is 37. And if I want the distance, I'm just going to take the principal square root of each side, and it'll be the square root of 37. Okay, so basically we've found that the distance between those 2 points is the square root of 37. Now, how can we generalize what we just looked at? Let me write this again. We had a squared, but I'm going to call this d squared, right? D for distance, is equal to, we had basically our 2 sides that were known. So we said b squared plus c squared. Let's go ahead and replace this, since when we have polar coordinates, we're going to have something like r sub 1, let's say theta sub 1, okay? And the r sub 1 is the length of a line segment or a side of the triangle. And then we also have the r sub 2 comma theta sub 2, okay? So what we're going to do is we're going to plug in, instead of the b and the c, I'll go ahead and just say this is r sub 1. I'm going to put this in parentheses because it gets kind of messy. So r sub 1, that's being squared. And this one will be r sub 2, this is being squared. It does not matter which point gets labeled as which, and I'll explain why that works out in a moment, okay? So then you're going to put the minus here, and then 2 times, again, it's these guys. Remember, with the formula, it was 2 times. In this case, it would be b times c. It's basically those 2 known sides. So I would say times r sub 1, and then times r sub 2, and then times cosine of the angle that you know. Now, in this particular case, remember how we found this? We subtracted, okay? So what I'm going to do is I'm going to say that I have theta sub 2 minus theta sub 1. The reason it doesn't matter here is that, let's say you end up with something that's negative. Remember, with cosine, you have this negative angle identity. So the cosine of negative theta, okay, if it ends up being negative, is the same as the cosine of theta, okay? So it doesn't matter if you produce a negative angle there, it's the same as if it would have been positive, okay? So you will get the same result either way. None of this stuff matters in terms of the order, right? You're just doing some simple operations here. So the order that you choose the points does not matter. Very important, okay? So this would be our formula. Of course, you could take the square root. So you could say d is equal to the square root of, and I could basically just copy all this. And let me go ahead and copy that real fast. And let me paste this in. And I'll just stick that underneath there so we don't have to write it. And let me just make that a little bit longer. And I'll just slide this down a little bit so it fits on the screen. Okay, so definitely something you want to copy down for your notes. And let's go ahead and just look at some examples. So we have 2, 120 degrees, and then 4, 210 degrees. Again, you can label these however you want. It comes out the same way. So let's say this is r sub 1, and this is theta sub 1. Let's say this is r sub 2, and this is theta sub 2. So the distance between the two, let me go ahead and write it out a few times so you get used to it. So r sub 1 being squared, plus you have your r sub 2 being squared, and then minus 2 times your r sub 1 times your r sub 2, and then multiplied by the cosine of the angle between them. So we're going to say theta sub 2 minus theta sub 1, okay? So let's just go ahead and plug in. We know that everywhere we see r sub 1, we're going to plug in a 2. So let's put 2 squared here, and let's put 2 here, okay? And then everywhere we see r sub 2, we're going to put 4. So let's go ahead and put a 4 there. We don't really need parentheses there. And let's put a 4 there. And then for theta sub 2 minus theta sub 1, you're going to have 210 degrees minus 120 degrees, which would be 90 degrees. So let's just go ahead and put cosine of 90 degrees. Now, most of you know that cosine of 90 degrees is 0, so you could basically get rid of this, right? So you can just erase this. You don't even need it because you'd be subtracting away 0, which doesn't change anything. So here we're just going to have the square root of 2 squared plus 4 squared. So 2 squared is obviously 4, and 4 squared is obviously 16, okay? And then if we add those together, we would get 20, okay? So the square root of 20, remember you can simplify this. We could say d is equal to, this would factor into 4 times 5, and 4 is a perfect square, right? So basically I can say this is 2 times the square root of 5. Okay, so that's going to be my answer for the distance between these 2 points. Again, if you change up the ordering, pause the video and you can see this on your own. The only difference is you're going to end up with the cosine of negative 90 degrees. And you could say that the cosine of negative 90 degrees is equal to the cosine of 90 degrees. In each case, and let me put my degree symbol in there so that's better. In each case, you're going to get 0. Okay, so remember this identity here. Let's take a look at another example. Here we'll work with some radians. So let's just go ahead and label this as r sub 1 comma theta sub 1. Let's label this as r sub 2 comma theta sub 2. And again, I'm just going to plug into the formula. So the distance is equal to the square root of, let's just go ahead and say r sub 1 is 3. So we'll say 3 squared plus r sub 2 is 2. So 2 squared, then minus 2 times, you can have r sub 1, which is 3, times r sub 2, which is 2, and then times the cosine of, this one's a little bit tricky because you do have to work with fractions here. So let me do this off to the side. I'm going to have pi over 2, and I'm subtracting away 7 pi over 6. Okay, I need a common denominator, so I'm going to multiply this by 3 over 3. So this would be 3 pi over 6. 3 pi minus 7 pi is negative 4 pi. So this would be negative 4 pi, and then over that common denominator of 6. And of course, you can reduce this fraction. This would end up being negative 2 pi over 3. Okay, so negative 2 pi over 3. Let's write that in here. Negative 2 pi over 3. Okay. Now, if you want to, remember, because of the negative angle identity for cosine, this is the same as if I had cosine of 2 pi over 3. So you can just get rid of the negative there. That way it makes it a little bit easier if you're working off the unit circle. And from here, I can just go through and evaluate things. 3 squared is going to be 9, and 2 squared is going to be 4. And basically you have 2 times 3, which is 6, times 2, which is 12. So this is a 12 here. 9 plus 4 is 13. Let's just go ahead and do that real quick. And essentially, the cosine of 2 pi over 3, remember 2 pi over 3 is 120 degrees, and we already know the cosine of 120 degrees is negative a half. So this is times negative 1/2. I like to wrap this in parentheses because basically you want to do this operation first. I know that's pretty obvious for most people, but I don't want you to get confused as to what's going on. So this is going to cancel with this and give me a 6 here. So basically you would have a negative 6, right? So what you end up with here is minus a negative 6, which is like adding 6. So 13 plus 6 would be 19. So basically here, the distance between these 2 points would be the square root of 19. All right, what I want to do now is look at 2 different examples where you have these negative angles and also the negative r values. This is a bit tricky for students to understand. You can basically just take what you have, okay, as it's given, and plug it into the formula, and it's still going to work, okay? So I'm going to use this directly as it's given, then I'm going to change it over, and I'll show you why it doesn't make a difference. So first and foremost, we have 4 comma negative 30 degrees. Let's say this is our first point. Again, it doesn't matter how you label this. I'll go ahead and say this is r sub 1 comma theta sub 1. And then let's say this 4 comma 210 degrees. Let's say that's the second point. So r sub 2 comma theta sub 2. Okay, so from here we just plug into the distance formula. So d, the distance between the 2 points, is the square root of. You're going to take this guy and square it, so 4 squared. Plus, you're going to take this guy and square it, so 4 squared. And then minus, you have your 2 times this guy, so 4 times 4, okay? And then times the cosine of the angle between them, okay? So what I'm going to go ahead and do is just say it's 210 degrees minus a negative 30 degrees, okay? Remember, minus a negative is plus a positive. So 210 degrees minus a negative 30 degrees, okay? And let me go ahead and close that down. And from here, we're just going to simplify, okay? So I'm going to say the distance between the 2 is equal to the square root of. This would be 16, and this would be 16. 16 plus 16 is 32. So let's write that. And then minus, you have 2 times 4, which is going to be 8, and then times 4 again, which is going to be 32. Okay, so you have 32 there. And then times, you're going to have the cosine of 210 degrees minus a negative 30 degrees is 240 degrees. So let me put 240 degrees there, okay? So let me just scroll down and get a little bit of room here so we can fit everything on the screen. So I'll say the distance is equal to the square root of. The cosine of 240 degrees, again, this is going to be in quadrant 3 now, and you're going to have a 60-degree reference angle. So this is going to be negative 1/2. Okay, so you would have 32 minus, you'll have 32 times negative 1/2. Again, if you want to make this clear, it's not necessary. You can wrap this in parentheses. It's kind of up to you. So I'm going to cancel this with this and put a 16 here. So basically you would have 32 minus a negative 16. That's why I like the parentheses there, so it makes that clear. So basically 32 minus a negative 16 is 32 plus 16, which is 48. Okay, so this is the square root, and let me make this a little bit smaller. This is the square root of 48. Of course, 48 is going to be 16 times 3, and 16 is a perfect square, right? It's 4 times 4. So you can go ahead and write this as 4 times the square root of 3, okay? So I'm going to say the distance is 4 times the square root of 3. Now, I want you to pause for a minute because some of you who try to plot this, if you go back up and you think about these points here, 4 comma negative 30 degrees and 4 comma 210 degrees, if you think about the angle between them, it's not 240 degrees. It's going to be 120 degrees. So why in the world did we get the right answer? And I'll show you in a moment that if you do it the other way, you'll still get the same thing. If we go to a little diagram here, you'll see that I've kind of drawn everything out. If you start at this point here, let me label this so everything's crystal clear. This point right here could be thought of as either 4, 330 degrees, or if you're rotating this way, clockwise, you could say that it's 4, negative 30 degrees, okay? And then this point over here, you could think about it again as 4, 210 degrees, okay? 4, 210 degrees, like this. Okay. So if we think about the angle between these, you can just look here. I've already kind of done this for you. But essentially, if you start at this 330 degrees and you subtract away the 210 degrees, you can see this angle between them would be 120 degrees, okay? The angle on the outside is going to be 360 degrees, one full rotation, minus this 120 degrees, which is 240 degrees. Okay, so that's if I started here and I rotate along the outside there. Okay, so that's 240 degrees. Okay, so we see that the angle should have been 120 degrees. So what in the world is going on? Well, it turns out that we have a little identity, and it states that the cosine of, let's say, 360 degrees minus some angle theta, okay, whatever it is going to be equal to the cosine of that angle theta. So this is exactly what we just came across. We see that the cosine of, let's say, theta is 120 degrees. So 360 degrees minus 120 degrees, okay, would be equal to the cosine of 120 degrees. This right here would end up being 240 degrees. So the cosine of 240 degrees is equal to the cosine of 120 degrees, okay? So it does not matter if I punch this in as 120 degrees for the cosine or 240 degrees, that value is the same. Okay, so when you go through and do your calculation, you're going to get the same answer, whether you work with it as is or you do a little conversion. Okay, now this little identity here can be quickly proven using the difference identity for cosine. Okay, so if you want to go through that, you could basically say that this guy right here, let me erase this real quick, and we'll go ahead and say that this is what? This is going to be the cosine of the first guy, so 360 degrees, okay, times the cosine of the second guy, so that's theta. Then remember, with the cosine difference identity, the sign is going to be opposite, right? So I'm going to make this a plus. And then I'm going to go ahead and say, now that I have the sine of this first guy, the 360 degrees, and then times the sine of theta. Now, I know the sine of 360 degrees is the same as the sine of 0 degrees, and the sine of 0 degrees is going to be 0, right? So you can basically get rid of this. This is going to be 0. And the cosine of 360 degrees is the same thing as the cosine of 0 degrees, and that's going to be 1. So you can get rid of this. This is a 1. So basically what you're left with here is 1 times the cosine of theta, which is just the cosine of theta. Okay, so that proves that little identity there. We can get rid of this and go back to this form. And let's go back now, and let's see what would happen. Let me go ahead and erase this. We'll keep this kind of here for now. Let's see what would happen if we converted this over. Instead of having 4, negative 30 degrees, let's add 360 degrees and say that our other point is now going to be, and I'll just write this over here, we'll say it's 4, 330 degrees. Okay, so I'm just going to put this over here and just line this out for a moment. And I'll say this is my r sub 1, theta sub 1. And maybe we can just erase this for now, just so it's clear what we're doing. And so in this particular case, what will we do now? Well, we're going to say that we still have the same 4 squared plus 4 squared, and then minus 2 times, you have your 4 times 4, okay, so that part's all the same, and then times the cosine of, this part would be different, so basically you have your 210 degrees minus your 330 degrees, which is negative 120 degrees. Again, remember, because of your negative angle identity with cosine, you could just make this positive 120 degrees, okay, it's going to be the same thing, and essentially we already know that the cosine of 120 degrees and the cosine of 240 degrees will be the same, right? We just saw that identity. So we know we would get the same answer. So we can go through here and just say, okay, well, this would be 16 plus 16, again, that's 32. And then minus, you'd have 2 times basically 16, which is 32. And then times the cosine of 120 degrees, we know, is again negative 1/2. Okay, so you can wrap this in parentheses, same thing we did before. This would cancel with this and give me 16. So this is negative 16. Again, you get 32 minus a negative 16, which is going to be 48. Okay, so we end up simplifying this, and we get the distance between the 2 points is 4 times the square root of 3. Okay, so it doesn't matter if you end up with a negative angle, you can work with your formula either way. Okay, let's look at an example with a negative r value. So again, you have the choice of working with it as is. Some people tell you to convert it. If you plug it into the formula, you will get the right answer, okay? So if you have something like negative 3 comma negative 165 degrees, and then 4 comma 45 degrees, if you wanted to, remember the little formula. If you have r and negative r, what you have to do is add 180 degrees to that, okay? So that's how I could change this over. I could say that this same point could be located by saying I have 3, comma, add 180 degrees to this, this would be 15 degrees, okay? So you can use either one. Let's go ahead and use the first one, and I'll show you it works the same either way. So the distance is equal to the square root of, let's call this point 1, so r sub 1, comma, theta sub 1. Let's call this point 2, so r sub 2, comma, theta sub 2. And again, all I'm going to do is just plug in. So I'd have negative 3, so negative 3, be careful there, being squared, plus you'd have 4 being squared, and then minus 2 times negative 3, okay, times 4, and then times the cosine of, if you subtract 45 minus a negative 165, that's like 45 plus 165, okay? We put my degree symbols in there. So that's going to give me 210 degrees, okay? So this is 210 degrees. Let me extend this a little bit over. All right, so let me put here that the distance is equal to the square root of. If I square negative 3, I get 9. If I square 4, I get 16. If I add 9 and 16 together, I'm going to get 25. Okay, so that's pretty simple. Here what I'm going to do is I'm going to say negative 2 times negative 3 is positive 6. And then positive 6 times 4 would be positive 24. So let me put plus 24 times the cosine of 210 degrees. Now 210 degrees, that's going to be in quadrant 3. Okay, so cosine's negative. And it's based on a 30-degree reference angle, okay? So the cosine of 30 degrees is square root of 3 over 2, and because we're in quadrant 3, this would be negative. So I'm going to say this is the negative of the square root of 3 over 2, okay? So if you multiply these together, what's going to happen is this would cancel with this and give me a 12, okay? And it's going to be negative. So I might as well just write minus, and I'll say 12 times the square root of 3, okay? Times the square root of 3. Now, you can approximate this if you want. If you want an exact answer, this is going to be it. All right, so let's work with this point. I'll show you it still works. So we'll go ahead and say, change that r value to positive. At 180 degrees to negative 165 degrees, that's 15 degrees. Let's line this all out. Let's get rid of that. And I'll label this as r sub 1, comma, theta sub 1, okay? So if you plug in, here the sign's going to change, and here the sign's going to change, okay? And this is going to change. Everything else would be the same, right? So basically what you'd have here is inside, now you do 45 degrees minus 15 degrees, okay? And that's going to give me 30 degrees. So I want you to notice that a moment ago, we had the cosine of 210 degrees, okay? And essentially, this had a 30-degree reference angle, but this guy is positive and the other guy's negative. But notice that you have a sign change here. Okay, before you had negative 2 times negative 3. Now it's negative 2 times positive 3. Okay, so I'm going to show you a little identity in a moment that proves that this is basically going to work, right? So if you add 180 degrees to your angle, okay, it's going to change the cosine of that from negative to positive, okay, or from positive to negative. So essentially what I have here is 9 plus 16, which is 25 again. So that part is the same, okay? And then here we have 2 times 3, which is 6, times 4, which is 24. So this is minus 24 now. You can put plus negative 24 if you want. Okay, and we're going to multiply this by the cosine of 30 degrees. We know that this is going to be the square root of 3 over 2, okay? And so from here, this cancels with this. Again, it's negative times positive, so it's still negative. So it's going to be negative 12. So negative 12, let me erase that and put negative 12, times the square root of 3. Okay, so you see you get the same answer either way, okay? So let's talk about why this works. Let's get rid of all of this. Again, when I think about something like the cosine of some angle theta plus 180 degrees, this is going to be the negative of the cosine of theta. So you saw with our example, we basically had a theta that was 30 degrees, right? If I added 180 degrees to that, I got 210 degrees, and that's going to be the negative of the cosine of 30 degrees, okay? Again, you can prove this with the cosine sum identity. So if you wanted to do this, you could say that you had what? The cosine of the first guy, theta, and then basically times the cosine of 180 degrees. Now, you know this is negative 1, so you can just replace that. Just put a negative out in front. And then you're going to go minus, right, because it's always the opposite sign. So it's going to be sine of the first guy, so theta, times the sine of 180 degrees. Now, the sine of 180 degrees is 0, so you can get rid of this, and you're just left with the negative of the cosine of theta. So it doesn't matter if you get a negative r value. If you change that over to a positive, then your angle is going to increase by 180 degrees, okay? So you're going to change the signs on the middle part, but then you're going to compensate for that because your cosine value is going to change signs as well, so you're going to come back to the same answer. In this lesson, we want to talk about the polar form of a line. All right, so we've spent a lot of time talking about the polar coordinate system and also how to convert rectangular coordinates to polar coordinates and then take those polar coordinates and plot them on the polar grid. What we're going to do now is take the next step and talk about polar equations, okay? So we're going to need to know how to convert between the rectangular form and the polar form, and we're also going to need to know how to graph these equations on the polar grid. So today we're going to start out with something very simple. It's the polar form of a line, and basically graphing them and converting them back and forth between the rectangular form and the polar form. Okay, so basically what you need to know is if you're going from your rectangular form to your polar form, it's very, very simple. You're going to use a relationship that we've talked about many times, and that's basically that the sine of theta, going back to the original definition, is y over r, right? You could say opposite over hypotenuse. And the cosine of theta is equal to x over r, the adjacent over the hypotenuse. What we're going to do in each case is multiply both sides by r. So I'll say this is r times sine of theta, multiply this by r, and that would cancel. So you've solved this for y here. Same thing over here, multiply this side by r and this side by r, this would cancel over here. And what you end up with is a relationship you're going to use to convert this, okay? So I'm going to take this right here, this r times sine of theta, and I'm going to plug it in for y. And then I'm going to take this right here, this r times cosine of theta, and I'm going to plug it in for x. That's all you need to do. Now, depending on your teacher, they may have you work with some generic form. So this is the standard form of the line. You also have the slope-intercept form, the y equals mx plus b. If you're working with this a lot, you may need to convert it over generically, okay? And then you can just plug in for your a, b, and c, okay? Or in this case, you would just be plugging in for your m and your b, okay? But it just depends on what you want to do. Let me just go ahead. I'm going to solve this generically. And then on the first example, what we'll do is we'll just plug it in that way. And then I'll also plug it in the other way. I'll show you it's the same thing, okay? So let's just go ahead and plug in r times cosine of theta here, and then r times the sine of theta here, okay? So what would we have? You would have a multiplied by r times the cosine of theta, plus you would have your b times your r times your sine of theta, okay? And this just equals c. Now the idea here is that you're going to factor out the r, okay? And then you're going to solve for r. So if I pulled that guy out, okay, if I pulled that guy out, I would have r times the quantity. What's left? Your a times your cosine of theta. So a times cosine of theta plus your b times your sine of theta. So your b times your sine of theta. And this is equal to c, okay? So let's stop for a minute. Let's scroll down and get a little bit of room going. How can we solve this for r? Remember, this whole thing is a quantity, and it is multiplying by r, okay? So what I can do is just divide both sides by this quantity, this a times the cosine of theta plus b times the sine of theta, okay, perfectly legal. And so what's going to happen is this is going to cancel with this. That will be 1. So you have r by itself, and it's equal to, and over here, let me scooch this down a little bit so this looks a little bit better. I'm going to divide this by the same thing. So a times the cosine of theta plus b times the sine of theta, okay? So r equals, you have your c, which is your constant from the ax plus by equals c, over your a times your cosine of theta plus your b times your sine of theta, where the a is the coefficient from x and the b is the coefficient for y. Now you could do a similar process with the y equals mx plus b, get yourself a general formula for that. It's up to you in terms of how many of these problems you're going to have to solve and whether it's worth it or not to use a general formula or just plug in each time, okay? But what I want to say is if you're going to use this formula, make sure that your line is in the format of ax plus by equals c. It must be in this format to use this formula. Okay, it's very, very important because a lot of times you get the slope-intercept form or something else given to you, okay, and people start plugging things in and they get the wrong answer. So let's go ahead and just look at a simple example. So here we have y equals x minus 4, Okay, this is in slope-intercept form. So this follows the y equals m the slope times x plus b the y-intercept. Okay, so we know this. If we want to convert this to standard form, so we can use that little formula, then what we would do is we would subtract x away from each side. Okay, so I would say that I have negative x plus y is equal to negative 4. Now for myself, I prefer the high school definition of the standard form of the equation of a line. And so I want the coefficient here for x to be positive. And to do that, I'm just going to multiply everything by negative 1. So this would be x minus y is equal to 4. Okay, it just changes the sign of every term when you multiply both sides by negative 1. Okay, so let me actually erase this and this. Okay, and at this point, basically you can use your formula. You know that the coefficient for x is a 1. The coefficient for y is a negative 1, and your constant is a 4. So in other words, the a value is 1, the b value is negative 1, and the c value is positive 4. So remember, r is equal to, you have your c over, you have your a times cosine of theta, plus your b times your sine of theta. Okay, if you do this a few times, you will memorize it. Now, what I'm going to do is just plug in. So instead of c, I have 4. Instead of a, I have 1, so you can just get rid of that. And instead of b, I have negative 1, so I can just change this to a minus. And that's all it is. So r equals 4 over the cosine of theta minus the sine of theta. Okay? Now you might be thinking, how in the world are we going to graph something like this? And I'll show you that in a moment. But really quickly, I just want to show you, if you had done this the other way, that you would get the same answer. Right? So basically, if I plugged in r times cosine of theta there, and I plugged in r times the sine of theta there, I could achieve this same result. Okay, so what I could do is say I have r times sine of theta, and then what I'm going to do is say I'm going to subtract this right here away from each side. So I'll say minus r times cosine of theta, and this is going to be equal to negative 4. Okay, and from here, what I'm going to do is I'm going to factor the r out. So I'll say r times the quantity sine of theta, and then I'll say minus the cosine of theta, and this will be equal to negative 4, okay? And then I'm going to divide both sides by this so that r is equal to, you'll have negative 4 over, I'm going to go ahead and say, I'm going to put negative cosine of theta first, and then plus the sine of theta, right? So the only difference between this and this is the sine. And of course, what you could do here is you could multiply the numerator and denominator by negative 1, okay? That's perfectly legal because that's a complex form of 1. So this would become positive, this would become positive, and this would become negative. And essentially what would happen here is your two forms would match up completely, right? R equals 4 over cosine theta minus sine of theta in each case. Okay, so let's erase all of this, and let's talk about graphing now. So graphing a polar equation is probably one of the most difficult things to graph. And with a line, it's a little bit more challenging. Lines are a lot easier to graph on the rectangular coordinate plane. To see this really quickly, let's think about y equals x minus 4 on the rectangular coordinate plane. We know that the y-intercept is going to be at 0, negative 4, and m, the slope, is equal to 1, right, the coefficient for x. So essentially, I could plot 0, negative 4, and then just use my slope of 1 to get additional points. So if I come here, I can see that I just drop down to 0, negative 4, that's right there. And then I can use my slope. So up 1 to the right one, up 1 to the right one, so on and so forth. I could generate this point and this point and this point. As many points as you need. You only need 2 points to get a line. A lot of times people like 3 to get a check, but you only need 2. Now let's say that I wanted to graph that equation in polar form on the polar grid. What could we do? Well, you can go back to your original strategy of making a table of values. So we would go back, just make a little table and say, okay, I have my r value and my theta value. And I like to plug in values for theta, okay, and then get a value for r. So what I'm going to do here is I already know that the y-intercept occurs at 0, negative 4. That's pretty easy to convert over. So this point right here, you can use the traditional method to convert it over. That's up to you. But what I'm going to do is just think about the fact that, okay, if I'm starting here at the origin, I need to travel 1, 2, 3, 4 units to get there, okay? And essentially, the angle here is going to be 270 degrees. I know the r value is 4, okay, not negative 4, but 4, and the angle is 270 degrees. So if I come back, I can say that a theta value of 270 degrees would give me an r value of 4. And you can check this out. if you plugged in a 270 degrees there and also there, what would you get? Well, the cosine of 270 degrees is 0, okay? So essentially you would have 4 over, you would have 0 minus. The sine of 270 degrees is negative 1, minus the negative 1 is 1, okay? So essentially you would have 4 there, right? So you would get 4 comma 270 degrees as one of your points, okay? Then the other one, if you think about your x-intercept here, well, again, you can go back to your graph that this guy right here is 4 comma 0, okay? So essentially from the origin, I have moved 1, 2, 3, 4 units to the right. So the r value is going to be 4, okay? But the angle here is going to be 0 degrees, right? Because I'm on the positive x-axis. So if I go back, that point would be 4 comma 0 degrees, okay? Again, you can plug this in. Plug in a 0 degrees here and a 0 degrees here. You would have 4 over. The cosine of 0 degrees is going to be 1. And then minus the sine of 0 degrees is going to be 0. So this would be 4 over 1, which is 4. Okay, so that's another point. So 4 comma 0 degrees. All right, so now that we have these 2 points, we're ready to sketch our graph. So again, our 2 points, we have the 4 comma 0 degrees. So that's going to be right here. And the other one is going to be 4 comma 270 degrees. So I'm going to be swinging around to right here. So that's right there. And then basically, once you have those 2 points, that gives you a line. So you can sketch that guy and you are done. Okay, let's look at another example. So here we have y equals negative 2x minus 6. Again, you can put this in standard form and use your formula. You can plug in for x and y, whatever you want to do. I'm just going to use the formula. So I'm going to add 2x to both sides of the equation. And I'll go ahead and say that this is 2x plus y is equal to negative 6. So my value for a is 2. It's the coefficient for x. My value for b is 1. And let me put that in visibly. Okay, that's going to be my coefficient for y. And then my value for c, my constant, is negative 6. Okay. So now I'm just going to plug into the formula. I'll say that r is equal to, you're going to have your c value, which is negative 6. So let me put a negative out in front. I'll put the 6 out up here. And then over, you have a, which is 2, times the cosine of theta. And then plus, you're going to have your b value, which is 1, so don't write anything, times the sine of theta. Okay, so that's all it is. So this is our equation. You can see that using that formula is pretty quick. And essentially, if I want to graph this, again, the simplest way for me to do this is to think about this on the rectangular plane. If I can get the x and the y intercept, that's going to give me 2 points that I can really quickly convert over to polar form, and I'm done. Okay. In some cases, you won't be able to do that. I'll give you an example of that later on. So here, what I'm going to do is I'm going to say, okay, well, the y-intercept, since this is in slope-intercept form, I know is at 0 comma negative 6. So think about this. If I was at the origin, I would be going down 1, 2, 3, 4, 5, 6 units to get there, okay? And from the positive x-axis, I'm swinging around 270 degrees. So essentially, my r value is going to be 6, and my theta value is going to be 270 degrees. And again, if you're not comfortable with what I'm doing, just take the normal steps to convert this that we talked about over the course of the last 2 lessons, okay? Then the other guy here, the x-intercept, if we think about that, well, if I plugged in a 0 there, I would have basically 0 is equal to negative 2x minus 6. Add 2x to both sides, so 2x is equal to negative 6. Divide both sides by 2, you get x is equal to negative 3. Okay, so this would be negative 3 comma 0. So in polar, what would that be? Well, negative 3, if I start right here, let's say we're going to go 1, 2, 3 units to the left. Okay, don't worry about it being negative. It's 3 units to the left. And the angle with the positive x-axis, we're going to come around 180 degrees. Okay, so this guy is going to be, let me kind of scooch this down a little bit. This guy is going to be 3 comma 180 degrees. Okay, so that's going to be my 2 points in polar. So if I come over here, again, I go out to a circle with a radius of 3. I'm going to swing around to a 180 degree angle. So there's that point there. Then for the other guy, I'm going to go out to a circle with a radius of 6, and I'm going to swing around here to an angle of 270 degrees, okay? Then you can just sketch a line through those 2 points. Okay, let's now talk about the harder scenario. This is where we're going from the polar form to the rectangular form. So when you work with this, you need to understand a few relationships. The first one is that the tangent of theta is equal to y over x. Just going back to that definition, you're going to need this a lot. Also, you're going to need to know that r is equal to the square root of x squared plus y squared. Again, we've talked about that a lot, and we'll see how to use these as we go forward, okay? For right now, I'm just going to use this relationship here, okay? And so I have that theta is equal to 2 pi over 3. Now, because my polar grid is written in degrees, I'm going to change this and say theta is equal to 120 degrees. Okay, I'm just going to convert that over. And essentially, when you see something that's theta is equal to k, this is a line that passes through the origin, okay? We're thinking about it that way. Now, how could I convert this over? Well, to convert it over, what I would do is I would first take the tangent of each side, okay? So if I take the tangent of each side, I would have the tangent of theta is equal to the tangent of 120 degrees, okay? Now pause the video and think for a minute about how you can get this into rectangular form. How can I get this into an equation with x and y? Now, if you gave that a shot, first I would say, okay, what is the tangent of 120 degrees? Well, it's the negative of the square root of 3. So let's erase this, or actually, let me keep this in line, and let me actually keep that step there in case people get confused. So the negative of the square root of 3. And over here, notice that I have the tangent of theta. Okay, this is the trick here. You're going to replace that with y over x, because the tangent of theta is equal to or the same as y over x. So I'll say y over x is equal to the negative of the square root of 3. So once you realize that, it's pretty easy from here. All I really need to do is multiply both sides by x. So multiply this side by x and multiply this side by x. And I'll say y is equal to, I'll say the negative of x times the square root of 3. So this is the rectangular form of that equation. Now, if we think about graphing this, again, if I had something that was theta is equal to 120 degrees, and you stop for a minute and think about that, you think about the fact that there is no r value given. So it means that no matter what the r value, whether it's positive, we know we can have negatives, that basically I'm going to be on a 120 degree angle. So if I think about starting at the pole here, or the origin, if I'm walking forward, I'm going to be on this 120 degree angle here. Remember how if you have a negative r value, you're walking backwards. So again, I would find 120 degrees and I would walk backwards, okay? So essentially here, r is greater than 0, and then down here, your r values are less than 0, okay? So again, this part is a little bit confusing. Again, if the r value is less than 0, and you had a 120 degree angle, you would find that angle, you would turn around, and you would walk this way, backwards. Now, you could also draw the same line by saying that theta is equal to 300 degrees, okay? So I know people would ask that because essentially, if I gave you that one, well now, the r value here would be positive, okay? Because here I'll be walking forward, and then the r values going this way would be negative, okay? So it's just a way to write the same line, okay? But there's different conditions there where r is going to be positive in one direction for this one, and r is going to be positive in a different direction for this one. Okay, let's look at a harder example. So this is one that takes a little bit of thought. So here we have r is equal to the cosecant of theta plus 45 degrees. All right, whenever you see cosecant or cotangent or secant, go ahead and write it in terms of sine or cosine and see if that makes anything easier for you, okay? Remember when we worked with our trigonometric identities, that was the general strategy, okay? So that's what we're going to do here. I'm going to say r is equal to, we know that 1 over the sine of theta is equal to the cosecant of theta, okay? That's the relationship. So I'm going to say this is 1 over the sine of theta plus 45 degrees, okay? Now from here, I can multiply both sides by this sine of theta plus 45 degrees, and that's going to give me that r times the sine of this theta plus 45 degrees, okay, is equal to 1. Now, again, we know that we can't just distribute this sign inside, right? We know that we have a sine sum identity, and we need to use that here, okay? So to do that, I'm going to put some brackets around this guy. And remember how this identity works. It's the sine of the first guy, so the sine of theta, times the cosine of the second guy, so the 45 degrees. Then you're going to have plus, you're going to go the cosine of the first guy, which is theta, times the sine of the second guy, which is 45 degrees. Okay, so go ahead and close that down, and this equals to 1. Okay, so from here, you see that it's getting a little bit easier because we know that the sine of 45 degrees and the cosine of 45 degrees is square root of 2 over 2. So all you have to do is replace that. So I'll say r times, I'll just use some parentheses here. I'll say the square root of 2 over 2, and then times the sine of theta, okay? And then plus, I'll say my square root of 2 over 2 times the cosine of theta, okay? And this equals 1. So from here, I need to do two things. Remember, we have this relationship where x is equal to r times cosine of theta, and y is equal to r times the sine of theta, okay? So if I distribute this r into each term, you notice that I could replace r times sine of theta with y and r times cosine of theta with x, okay? Also, I'd want to factor this guy out at the same time. I know I'm doing two steps in one, but I think you're strong enough to get that, okay? So what I'm going to end up doing is I'm going to pull this out. So I'm going to say I have the square root of 2 over 2. And then I'm going to distribute the r in. So I'm going to have r times sine of theta. And then plus I'll have r times cosine of theta. And of course, let me make these parentheses a little bit better. I'll say this is equal to 1. Now, from here, again, r times sine of theta, that's just y. R times cosine of theta, that's just x. So what I'm going to do is say I have square root of 2 over 2 times I'll have basically y plus x. You could rearrange that as x plus y. It's really up to you. And then I'll say this equals 1. Now, what I'm going to do is multiply both sides by 2 over square root of 2. So times 2 over square root of 2. This is going to cancel. And this is going to give me, I'll just go ahead and write this as x plus y is equal to, I'll have 2 over square root of 2. And of course, we always want to rationalize the denominator. Let me move this over a little bit. So I'll multiply this by the square root of 2 over the square root of 2. And what's going to happen is this down here would become 2. So this would be 2. And up here, this would be times the square root of 2. Well, notice that now you can cancel this with this. So I'm just left with the square root of 2. Okay, so here we have x plus y equals the square root of 2. Now, let's talk about graphing this. So if we have x plus y is equal to the square root of 2, from here I can figure out that my x-intercept would be what? Well, if I plugged in a 0 for y, I would basically say that the x-intercept would be square root of 2 comma 0, and then basically my y-intercept would be what? It would be 0, right, if I plug that in for x, comma square root of 2, okay? So again, these are easy to convert over. Now, the square root of 2 is something you have to approximate. Most people will say this is about 1.41, okay? So I'll go ahead and say that I have about 1.41, comma 0, and then I'll have 0, comma, about 1.41. Okay. Now, let's say we wanted to convert these over to polar form. For this one, I know that if I just start at the origin and I'm just going to the right by 1.41 units, my angle is going to be 0 degrees and my r value is going to be 1.41. So this is 1.41, comma 0 degrees, okay? For this one, I'm going to be going up. So from the origin, I'm going to go up by 1.41 units, okay? So my r value, again, is 1.41. And my theta value here, the angle, if I think about it this way, right, that's going to be 90 degrees. So this is 90 degrees, okay? Now you can go back and check this. Let me grab this real quick. We'll come back up here and paste this in. You can check these real quick. If you put in 0 degrees there, the sine of 45 degrees is square root of 2 over 2, okay? And if you think about it, you have 1 divided by that, so you're just flipping it. And so you're going to end up with 2. You're going to end up with 2 over the square root of 2. Again, rationalize the denominator, okay? And you're going to end up with just the square root of 2, okay? So a 0 degree angle for theta gives me square root of 2 for r, okay? So we know that. And then the other one, you can do this one. You plug in 90 degrees there. Well, 90 degrees plus 45 degrees gives you 135 degrees. You still have a 45 degree reference angle, so it's going to be the same thing, right? So basically, I'm going to end up with an r value of square root of 2. Okay, now if you wanted one other point, you can think about your unit circle here, and something that would work pretty nicely. You know that the sine of 30 degrees is equal to 1/2. And so if I could make this bottom part 1/2, okay, somehow, some way, 1 divided by 1/2 would be 2. That would be a nice point to plot, okay? So what I could do, I could think about, okay, well, sine of 150 degrees has a 30 degree reference angle. Sine of 150 degrees would also be 1/2. And what I could do is I could add 105 degrees. So I could put 105 degrees in there, okay? So I would have sine of 105 degrees plus 45 degrees is 150 degrees, okay? And the sine of 150 degrees is 1/2. So then your r value there would basically be 2, right? Because 1 divided by 1/2 is 2. And the theta value here, don't plug in 150 degrees. It's what you're putting in here for theta, okay? So theta is 105 degrees. That's what you put in there. Be very careful. A lot of students make that mistake. When you're plugging something in for theta, that's what's going in here. I am plugging in 105 degrees. I am not plugging in 150 degrees. 150 degrees is the result that comes from adding 45 degrees to 105 degrees. Okay, so very important to make that clear. Now, once you have these 3 points, you can go ahead and sketch this guy. So let's go ahead and say that this point right here is going to be my point, which is an R value of, let's say, 1.41 approximately. And then I'll say the theta value is 0 degrees. Okay, so that's 1 point. Then this point right here is going to be my R value of 1.41. Okay, so you notice how it would be on the same circle there. Okay, and then basically the angle here is 90 degrees. Okay, so you can see that. And so let me draw an arrow to that. And then also we have this point right here. If you go out to a circle with a radius of 2 and we swing around to this 105 degree angle, remember you want a 105 degree angle, not a 150 degree angle, but a 105 degree angle. This guy right here would be a point 2. So you would have 2, 105 degrees, okay? You're just finding some points and then sketching a line through the points. All right, let's also talk about horizontal and vertical lines to wrap things up. So if you get something like y equals b, you know this is a horizontal line, right? So basically, no matter what the x value is, y always equals that constant b, okay? And essentially for this, I would just say, okay, well, I have r times sine of theta. Just plugging that in for y there is equal to b. And I would divide both sides by the sine of theta, okay? So both sides by the sine of theta. And so if you see something like r is equal to some constant b over the sine of theta, you know that you have a horizontal line, okay? That's very clear. And I'll show you an example of this in a moment. Let's also look at the vertical line. So you know if you have something like x equals a, this is a vertical line. No matter what the value is for y, x always equals that constant a. So here I'm just going to plug in r times cosine of theta. And essentially I would have r times cosine of theta is equal to a. Divide both sides by the cosine of theta. So divide by the cosine of theta. So you get r is equal to a over the cosine of theta. Okay, so this is your vertical line in polar form. All right, let's look at 2 quick examples. So we see here we have y equals 3. To convert this over, again, if it's a horizontal line, then I know it's going to be r is equal to, you're going to have this constant here, which is 3, over the sine of theta. Okay, that's all it is. And to graph this, it's no different than when you graphed it on the rectangular coordinate plane. You would basically just go up from the origin 3 units, okay, by this number of units, and make a horizontal line. If you go here, and you look at this guy, you can start here. I go up to a circle with a radius of 3, so I'm right there. So basically 1 point of the line, and we'll verify this in a second, would be 3 for the radius and then 90 degrees for the angle, okay? So that guy would be on that line, and then essentially you would just draw a horizontal line there. Some other points you would have 6, comma, you would have 30 degrees, okay? And then another point you could see that you would have 6, 150 degrees. Notice that 150 degrees has the same reference angle, and also since sine is positive in quadrants 1 and 2, it would have the same sine value, right? In each case, it's a half. So if we go back and we think about, does this work? Well, the sine of 90 degrees is 1, so 3 over 1 is 3, so that works, right? Basically, if I plugged in 90 degrees there, my r value would be 3. And then if I did r is equal to 3 over the sine of 30 degrees or the sine of 150 degrees, well, in each case, this would be a half. And essentially, you would have 3 times 2, which is 6, okay? So there you would get 6, 30 degrees or 6, 150 degrees. All right, so lastly, we have x is equal to negative 3. So following the formula, we'll say r is equal to, we'll say negative 3. We'll go ahead and say that's divided by the cosine of theta, okay? So before we go to the graph, again, if you think about a point that's going to work, think about your coordinate plane. If this is 0, 0, if I want the x-intercept, which is going to occur at negative 1, negative 2, negative 3. So this point right here on the rectangular would be negative 3, 0, right? So if I'm drawing a vertical line, this is where it's going to cross. Now, if you think about this, this is going to be what? It's going to be an r value of 3. And then again, this angle here is going to be 180 degrees. So you can stop and plug that in and see if it works. The cosine of 180 degrees is negative 1, right? So essentially we would have negative 3 over negative 1, which is going to be equal to 3. Okay, so that gives me that point right there. You could grab other points. You know that the cosine of 120 degrees is negative a half, and then also the cosine of 240 degrees is negative a half. So if you did something like, let's say, 120 degrees, and then also 240 degrees, what's going to happen is you're going to be dividing by negative 1/2, which is like negative 3 times, you'll do negative 2, which is 6. Okay, so this would be some points, and I know that 6 and 3 don't match up, but remember, we're on the polar grid. So if we look at this guy, you can see that from here, you're basically going to go out to a circle with a radius of 3, and then swing around to a 180-degree angle. So there's your x-intercept as it would be on your rectangular coordinate plane. Here it's going to be at 3, 180 degrees, okay? From there, you can basically make a vertical line, but I just want to show you again, this point right here would basically be going out to a circle with a radius of 6, swinging around to a 120-degree angle, or going out to a radius of 6 and swinging all the way around until you get to 240 degrees, so that's that point there. In this lesson, we want to talk about circles in polar form. All right, so in this lesson, we're going to learn how to convert back and forth between the rectangular form of a circle and the polar form of a circle. We'll also look at some strategies to graph a circle on the polar grid. So I'm going to start off with a circle whose center is at the origin. This is the easiest scenario. And we're going to think about converting this back and forth. Now, first and foremost, when you work with polar form, you have that r. Okay, so remember, if you have something like the cosine of theta, we say this is x over r. If we have the sine of theta, we say this is y over r. And if you multiply both sides by r in each case, you would get r times cosine of theta is equal to x, and then you would get r times sine of theta is equal to y, okay? So what I'm going to do here, instead of having this r squared in rectangular form, I'm going to replace this with an a, okay? So the a is now going to be the radius in rectangular form, okay? So I'm going to say this is x squared plus y squared is equal to a squared. So that's typically the letter chosen in your textbook. So what I'm going to do now is think about the fact that, okay, if I want to convert this to polar form, I can always plug in r times cosine of theta anywhere I see an x, and I can plug in r times sine of theta anywhere I see a y. Okay, so this is the longer way. Some of you already know that x squared plus y squared is equal to r squared. Okay, we use this when we convert our rectangular points to polar points. So we already know this relationship. But let me show you this real quick. So if I plug in here, I would have r times cosine of theta being squared. Then plus you would have r times sine of theta being squared equals a squared. Okay, so because this is multiplication here, you can bring this in. So you can say this is r squared times cosine squared theta, then plus r squared times sine squared theta, and this is going to be equal to a squared. Now, the idea here, if you want to show that basically this side here is basically r squared, then you can just factor this out, okay? So pull this out in front of a set of parentheses, so r squared here times the quantity, what's left? Well, what I'm going to have is my cosine squared theta, so cosine squared theta, then plus my sine squared theta, and this equals a squared. So let me scroll down for a moment, get some room going. And I want you to think about the fact that this is the Pythagorean identity where you have sine squared theta plus cosine squared theta is 1, right? And if you reverse that, it's the same. So this is 1. So I can go ahead and just cross this out and say it's 1, and you see that x squared plus y squared is just going to give us r squared, okay? So now I have r squared equals a squared, okay? And here comes the confusing part. If I solve this for r, what I end up with is I end up with r is equal to plus or minus a. Now this result here is confusing because when we work with this in the rectangular coordinate plane, we don't have a negative radius. It doesn't make any sense. But if we think about this in polar, we can have a negative radius, so it's allowed. So basically we're going to see this. Some books will actually write just r equals a, and I'll explain this when we get to a problem, how you're going to end up with the same graph either way. All right, let's go ahead and look at a simple example. So we have x squared plus y squared equals 25. So again, this matches your format of x squared plus y squared is equal to, again, the radius here, we're going to call it a, so a being squared, okay? And this converts over to, you would basically have your r is equal to plus or minus a. And what you have to consider here is 25 is not a, it's a squared, right? So what I would want to say is to convert this over, I could quickly just say this is r is equal to plus or minus 5, right? That's all you would really need to do. Again, if you want to do this the long way, I want you to consider the fact that we just showed that r squared is equal to x squared plus y squared, okay? So basically I can replace that with my r squared, and this equals 25. And again, if you solve for r equals plus or minus 5. So however you want to do this, you can do it this way, which is a bit longer, or you can just use your formula if you have it memorized. All right, let's talk about graphing this guy now. So essentially, people get a little bit confused. If you have something like r is equal to, let's just say 5 for right now, what would I do? Well, there's no theta involved. People are always trying to plot points with theta and r. There is no theta. So that just means no matter what the theta is, no matter what the angle is, the r value is always 5. So starting from the pole, okay, let's say that theta was 15 degrees, I just walk forward by 5 units, right? So I'm going to be on this circle with a radius of 5. Okay, and then if I was at 30 degrees, I'd be on a circle with a radius of 5, so on and so forth. You're going to end up basically tracing a circle through those points that are formed to get this graph here. Okay, that's all you're doing. Now, if you consider r equals -5, remember, if you had a point, let's just say it was 5, 45 degrees. Okay, so that's going to be coming out to 5, a circle with that radius, swinging to 45 degrees. That's right there. Okay, consider that you could locate the same point by saying you had -5, 225 degrees, right? So in other words, if I'm facing this way, right, I swung all the way around to this angle right here, okay? Well, what I want to do is go backwards now. So I want to go this way by 5 units. So you can trace out the exact same points using that logic. So r equals -5 there would be the same circle, okay? So that's why a lot of people will just drop this one and say, okay, this is the graph of r equals 5. But again, some teachers want you to put r equals plus or minus 5 like this, just because you can have a negative radius with the polar grid. All right, let's go ahead and take a look at an example where we have an equation of a circle that's centered at the origin and it's given to us in polar form. We're going to put this in rectangular form. We're also going to graph this on the polar grid. So we have that r is equal to plus or minus 6. And remember, we can say that x squared plus y squared equals a squared can be converted to r equals plus or minus a. So now we're going backwards here. So we have the r equals plus or minus a. In this case, a is 6. We want to go to this form. So I would just say I have x squared plus y squared is equal to, go ahead and square a. A is 6, so that's going to be 36. Okay. Another way you could do this, if you don't like using these formulas or maybe they're too tough to memorize, you can just square both sides. That would give me that r squared is equal to, if I have positive 6 or negative 6 and I square it, I get 36. Remember, whenever you have r squared, you can replace that with x squared plus y squared, okay, going over to rectangular, and this just equals 36. So either way, you're going to get the same answer. Now, graphically, again, this is very easy to do. So r equals plus or minus 6. From the origin, or from the pole, if you want to think about it that way, essentially I'm just walking forward by 6 units. Okay, so I'm going to a circle with a radius of 6 in each case, no matter what the angle is. Okay, so I would trace out a series of points. Okay, and again, you can trace out the same points using a -6 for the radius. So then you sketch your graph by tracing a circle through those points, and you're done. All right, in most cases, we're not going to see a circle whose center is at the origin. A lot of times, though, the circle will pass through the origin, and so most of our problems will involve that scenario. So I'm going to start off with something generic here. You'll see this in most textbooks. Let's say we had a circle that was not centered at the origin, okay? And essentially what I'm going to say is that the center of that circle is going to be labeled as p sub 0, and then the polar coordinates for that point would be r sub 0 and then theta sub 0. So the distance from the origin, which we labeled as O, to this point, which is the center, p sub 0, okay, would be r sub 0. So that's the length of this side right here. Okay, so that's given by this r sub 0. And the angle here is going to be theta sub 0, okay? So we've got that part. Now, the other thing is we can have ourselves a little point on the circle. So let's call that p, okay? And the coordinates there in polar are going to be r comma theta. So the distance from the origin to that point p, okay, would be r. Now, the angle there, this guy right here, would be theta. So we have those two things. Now, if I want to figure out what is the length of A, which is the radius of this circle, okay, or the length from this guy right here, this point P sub 0, to this guy right here, some point on the circle P, well, what I can do is I can use my law of cosines, right? Because I have the length of this side here, which is r sub 0. I'll have the angle here, which is going to be given by theta, okay, the bigger angle here, minus theta sub 0, which is the smaller angle here, okay? And then we'll have this side here, which is r. okay? So I have side, angle, side. So what I can do to get the length of this side A is set up my little law of cosines here. So A squared is equal to, you have your r sub 0 being squared plus your r squared minus your 2 times r sub 0 times r times the cosine of theta minus theta sub 0, okay? Now, we're not going to actually work with this guy. What we're going to do is we're going to think about the first scenario where our circle passes through the origin, okay? So now consider the fact that, again, from the origin, if you called that the point O, to this guy right here, which we said was P sub 0, okay, the coordinates here now are A, comma, 0 degrees, okay? So your theta is going to be 0 degrees, and your r sub 0 is going to be A, right? Because the distance from the origin to the center is now going to be equal to the radius. So if we go back, this allows me to plug in for this r sub 0. I'm going to plug in an A, and then I'm going to plug in an A. Okay, so we can simplify this. In this case, we would have A squared is equal to, you'd have A squared there, plus r squared minus 2AR times the cosine of, if I plug in a 0 there, that's basically gone, right? So I just have cosine of theta. So from here, you can notice that this would cancel, and you could move the r squared to the other side. So negative r squared is equal to negative 2AR times the cosine of theta. I can multiply both sides by negative 1. So essentially, I just have r squared equals 2AR times the cosine of theta. Now, here's where everybody gets a little bit lost. Normally, if you have something squared, you take the square root of each side. In this case, we're going to divide both sides by r, okay? Because r squared divided by r is r by definition. And so this is going to cancel here, okay? And I'll have 2a times the cosine of theta, okay? So if you go back to this little diagram here, you'll see r equals 2a times the cosine of theta. So that's going to give me a circle that passes through the origin that has a center on the x-axis, okay? And it's all based on the fact that the distance from the origin to the center is given by this a here, okay? That's the radius of this circle, okay? Now, another way that you can derive this, if you don't like the geometric definition or going through all that stuff, you can think about this in rectangular form. This a comma 0 degrees here would be a comma 0. And then it's easy to achieve this result. I would say, okay, well, I would say x minus a quantity squared plus you would have y minus 0 quantity squared is equal to, in this case, the radius is a, so a squared, okay? Let me go ahead and copy this real quick. Basically, what you'd want to do first is expand this. So you'd want to say you have x squared minus 2ax plus a squared plus y minus 0 is just y, so this is y squared. This equals a squared. You see, again, you have the same thing on each side. So get rid of this and this. That's gone, okay? So now, I know if I have x squared plus y squared, again, that's r squared. So you can rearrange things if you want to make that crystal clear. So x squared plus y squared, and then minus 2ax would be equal to 0. Okay, let me put this visibly because some people get confused. You cancel that over there, it's 0. So let me replace this with r squared, and let me add 2ax to both sides. And now, what you do is, for x, remember, if you have x, you can always replace this with r times cosine of theta, okay? So I'm going to put this as r times cosine of theta. And again, the confusing thing here is that instead of taking the square root of each side, I'm going to divide both sides by r. That's something you just have to remember, okay? So what I'm going to do is basically cancel this with this, cancel this with this, and say, let me scroll down a little bit, that I end up with r is equal to 2a times the cosine of theta, okay? So if you see something in polar that looks like this, you can immediately convert it over and say it's x minus a squared, okay, that quantity squared, then plus y squared is equal to a squared, okay? Now, converting back from this one to this one is a little bit more tricky. You have to check to make sure that everything matches up, and I'll show you that in an example. Okay, let's take a look at the first example. So we have x plus 2 quantity squared plus y squared equals 4. Okay, so the first thing is, if you want to make sure that this matches, the x minus a, quantity squared, plus y squared equals your a squared. Again, think about rewriting this. You have a plus here. How can I rewrite that? You want to do minus a negative. So you just want to match this and see if it works. So x minus a negative 2, quantity squared, plus y squared is equal to, you basically have negative 2 being squared. Does this match? Yes. Now, if you saw something like, let's say this was 5, Would this work out? No, because if I'm saying this is -2, well, -2 squared is not 5. Okay, so you have to pay attention to this if you're going to use these shortcuts. Okay, so what I would have here is that a, my value for a, is equal to -2, not +2, -2. So when I set this up, remember, we said that r was equal to 2 multiplied by a multiplied by the cosine of theta. Okay, so here a is -2. So when I convert this over, I can just say that r is equal to basically 2 times -2 is -4 times the cosine of theta. Okay, once you do this a few times, it becomes very, very easy to convert these over. Let me erase all this real quick. And I'm just going to show you that you get the same thing if you do this the long way. So let me move this up here. With these, it's more of a time saver versus when you looked at the ones that were centered at the origin. So first I'm going to expand this. This would be x squared plus 2 times x times 2 would be 4x plus 4 plus y squared equals 4. Okay, again, you get this duplicate on each side, so you get rid of that, and this is 0. Okay, so now you have x squared plus y squared. Okay, that's going to be replaced with r squared plus 4x equals 0. Okay, so from here, what I'm going to do is I'm going to replace this with r squared. I'm going to subtract 4x away from each side. Okay, and all I really need to do now is replace x with r times cosine of theta. So r times cosine of theta. And again, this is the key. We're going to divide both sides by r. Okay, do not take the square root of each side. You want to divide both sides by r. So this is going to give me that r is equal to, again, this cancels, -4 times the cosine of theta. So however you want to do this, you're going to get the same answer. Okay, just make sure that if you're using the shortcut, that things match up. If this was 5 or 6 or 10 or something like that, this would not work. This would not be a circle that goes to the origin that is centered on the x-axis. This is where this formula works. Now, if you wanted to graph this, this is a lot more difficult, or a lot more challenging, I would say, versus when you worked with graphing a circle on the rectangular plane. The reason is, when you work on the rectangular plane, you can plot your center, and then from your radius, you can just move up by that amount, to the right by that amount, down by that amount, and then left by that amount. And then you can draw your circle, right? You're done. With this guy, you basically have to make some points, okay? So let me put an r value and then a theta value here. And you just have to use some logic, okay? So first off, I'm always going to try the cosine of 0. I know that's 1. So let me put 0, and I'll do this in terms of degrees. So 0 degrees, okay? So the cosine of 0 degrees is going to be 1. -4 multiplied by 1 would be -4, okay? So 1 point would be -4, 0 degrees. Another point, I always try 90 degrees because I know cosine of 90 degrees is 0. So that would be -4 times 0, which would be 0. So if I put 90 degrees, I would get 0. Okay, so basically this point would be 0, 90 degrees. That's just going to be on the pole, okay? Then other things you could do, if you had this as a half, right? -4 times a half would give you -2. If you want something that's positive for the r, then you're looking for -1/2, okay? So you know that cosine of 60 degrees is a half. But if you want it to be negative, it's got to be in quadrants 2 or 3. So you'd want something like 120 degrees, okay, which is a 60-degree reference angle in quadrant 2, or 240 degrees, which is a 60-degree reference angle in quadrant 3. So now I would say, okay, well, the cosine of either 120 degrees or 240 degrees is -1/2. -4 times -1/2 is 2, okay? So this is 2 and this is 2. So there's 2 more points. So you have 2, 120 degrees, and then you have 2, 240 degrees, okay? So let me grab these real quick. Let me copy them. All right, so obviously I've already graphed this guy, okay? But I just want to show you how you can do this. So we have -4, 0 degrees. I would convert this and say this is 4, 180 degrees, just to make it simpler. And essentially that would be what? So I would go out to a circle with a radius of 4 and then swing around to 180 degrees, so right there. And then 0, 90 degrees. Doesn't matter the angle. If you have a radius of 0, you're not going anywhere, right? So from the pole, you're stuck, right? So it doesn't matter which way I'm looking or turning or orienting myself. I'm just going to be on the pole, okay? Then 2, 120 degrees or 2, 240 degrees. So in each case, you're going out to a circle with a radius of 2. And then I'm going to swing around to 120 degrees. And then I'm going to swing around to 240 degrees, okay? So from those 4 points, that's enough to sketch the graph of that circle. If you're using a computer, obviously it's going to be perfect. But if you're doing it freehand, just notate your little points there so you can show the teacher you found some points and then sketch the circle the best way that you can. Okay, let's look at another example. So here we're given this guy in polar form. So r equals 6 times cosine of theta. Now, be very, very careful. when you look at the formula, remember it's r is equal to 2a times the cosine of theta. 6 is not a. Okay, you have to do some extra work here. You would say that, okay, well, this guy right here is equal to this guy right here. Okay, so 2a is equal to 6, which means if you divide both sides by 2, a is equal to 3. Okay, so once you know that a equals 3, converting this over is pretty quick, right? So let me write here that a equals 3. What I would do, I would say, okay, well, I know that we have this form of r equals 2a times the cosine of theta, and this goes to x minus a quantity squared plus y squared is equal to a squared. Okay, we know that. So here I'm just going to plug in. Everywhere I see an a, I'm just going to put a 3. So this would convert itself over to x minus 3 quantity squared plus y squared is equal to 3 being squared, which is 9. So that's the quick way to do it. But again, you've got to make sure that you match things up correctly. If you want to ensure against a mistake, then you can always do this the long way. So what I would do here is I would multiply both sides by r. So that gives me r squared, okay, which we can replace. And it gives me 6 times r times cosine of theta. Remember, whenever I see r times cosine of theta, I can replace that with x. And whenever I see r squared, I can replace that with x squared plus y squared, okay? So I'm going to have x squared plus y squared is equal to 6x. What I'm going to do is move this over to the other side. So I'll say I have x squared, and then I'll say minus 6x because I'm subtracting this away from each side. And then I'm going to leave a space because we're going to need to complete the square. Then plus y squared, and this equals 0, okay? So let me get rid of all of this, just so I have a lot of room to work. Get rid of this, and let's move this up. So maybe it's been a while since you completed the square, but remember, what you want to do is you want to look at this coefficient right here. In this case, it's -6. It's always the one on the variable to the first power, okay? So x to the first power. So -6, you want to cut it in half or multiply by half, and then you want to square the result, okay? So -6 divided by 2, or -6 times a half, is going to be -3. So then -3 squared is equal to 9. Okay, so from here I'm going to add 9 to both sides to make this legal. You can't just add it to 1. And essentially what I'm going to have here is a perfect square trinomial on the left-hand side. Okay, I don't need to do anything here because this is just y squared. Can't do anything with that. So with this one, I'm going to go, okay, x minus 3, quantity squared is how you'd factor that, then plus y squared is equal to 9. Okay, and again, it's easier if you use the formula, but sometimes if you're not super familiar with how to work with the formula, you might as well just go through this to guard against any mistakes. Okay, so let me erase, and let's talk about graphing this guy. So again, I would put some points here, so r and then theta, okay? So if I'm thinking about some thetas, I'm always going to go with 0 degrees. Cosine of 0 degrees is 1, so r would be 6. Then if I think about, let's go ahead and do 90 degrees, okay? Cosine of 90 degrees I know is 0. 6 times 0 is 0, so r is 0. Okay, so it's going to be at the pole. Again, let me think about the cosine of 60 degrees is going to be a half, right? So 6 times a half is 3. Okay, I'm trying to get some whole number values here. So I could do 60 degrees, okay? That would give me 3. And then also cosine is positive in quadrant 4 also. So I could do 300 degrees. That has a 60-degree reference angle. And I'm going to get 3 here as well, okay? So this would give me 6, 0 degrees. This would give me 0, 90 degrees. This would give me 3, 60 degrees. And this would give me 3, 300 degrees. And again, if I want 6, 0 degrees, well, basically from the pole, I'm just walking to the right 6 units, right? So I'm going to be right there. And then 0, 90 degrees, again, if the radius is 0, I'm not moving off the pole. And then 3, 60 degrees, again, I'm going to go out to a circle with a radius of 3 and then swing around to 60 degrees. So that's right there. And then 3, 300 degrees, circle with a radius of 3. And I'm going to swing all the way around to this 300 degrees right here. And again, these are enough points here to where you can plot them and then sketch a nice little circle through the points. Again, it doesn't have to be perfect. Just notate your points so your teacher can see that. All right, so another common occurrence is going to be a problem where the center is on the y-axis and the circle is going to pass through the origin. So in other words, from the origin, which is a point on the circle, to our center, okay, is going to be a distance of a. So that's going to be the radius, okay? So the center occurs at a comma, in this case, could be a 90-degree angle, right? If I'm thinking about this, this is a right angle, so it's 90 degrees. And essentially, if I wanted to come back up here, I would change only a few things. So let me get rid of this. And now this would be 90 degrees that I'm plugging in here, so that's a change, okay? So first, let's go through and do the cosine of, we'd have theta minus 90 degrees. Remember, this is going to be your difference identity for cosine. So it's the cosine of the first guy, which is theta, times the cosine of the second guy, which is 90 degrees. Let me write that a little bit better. So what is the cosine of 90 degrees? Well, we know that's going to be 0, so you just get rid of that, right? But I'm going to leave it for right now. So plus, then you're going to have the sine of the first guy, which is theta, and then times the sine of the second guy, which is 90 degrees, okay? So we know this is gone, and we know that the sine of 90 degrees is 1, so you'd say that's 1. So basically, this is going to end up being sine of theta, okay? So what I'm going to have here, I know that this would be a squared and this would be a squared, so get rid of it. I'm just going to say that I would have 0 is equal to r squared minus 2ar, okay? Instead of cosine of theta minus 90 degrees, we know that this is the sine of theta. So sine of theta, okay? Let me move this over. So negative r squared is equal to negative 2ar, and then times the sine of theta. Let's get rid of this. And I'm just going to get rid of this right here, okay? Let's move this up like this. And I'm going to multiply both sides by -1, get rid of the negatives. And essentially from here, I'm just going to divide both sides by r, okay, like I keep doing. So what's going to happen is this is going to cancel with this is going to cancel with this, and you get r is equal to 2a times the sine of theta, okay? So if r equals 2a times the cosine of theta, it's going to pass through the origin, and it's going to be centered on the x-axis. If r equals 2a times the sine of theta, it's going to pass through the origin, and it's going to be centered on the y-axis. Again, if we go back to this guy, you can erase this. If you think about these coordinates here in rectangular, this would be what? It would be 0, that's the x location, and then the y location would be a. So now if I think about this in rectangular, you would have x minus 0 quantity squared, plus you would have y minus a quantity squared is equal to, again, the radius here is a. The distance from the origin, or a point on the circle, to the center is going to be given by a. So I can say this is a squared. Okay, so let me grab this real quick. So what I'll do from here, I'm going to write this as just x squared, because obviously x minus 0 is just x. Then plus, I'm going to expand this, so this will be y squared minus 2 times y times a. So let's write minus 2 times a y, then plus a being squared, and this equals a squared. So you'll notice that, again, I could subtract a squared away from each side. So basically, let's just line this out and put a 0 here, okay? And then from here, I'd have x squared plus y squared. We know we can replace that with r squared. Let's do that in a second. I'm going to say this equals to, I'm going to move this over here. So I'm going to add 2ay to both sides. So I'm going to put 2ay like this. And now all I need to do is take x squared plus y squared, replace that with r squared. And then the 2ay, I'm going to put 2a and replace y with r times the sine of theta, okay? And then for the last step, I'm just going to divide both sides by r. So let me scroll down to get a little bit of room going here. And all we're going to do is just cancel one of these with this and this with this. And I'll say r is equal to my 2a multiplied by my sine of theta, okay? Let me make that s a little bit more clear. All right, so for our example, we'll look at r equals -4 times the sine of theta. So again, if you see something that looks like r equals 2a times the sine of theta, this guy's going to pass through the origin, and it's going to be centered on the y-axis. Okay, so again, don't just take -4. 2a, this part right here, let me do this in a different color so this is clear. So 2a is going to be equal to -4. So that means that basically you have 2a equals -4, divide both sides by 2, a equals -2, okay? So make sure you understand what you're plugging in. So if a equals -2, and you want to plug into that formula, so we're going to have x squared plus, you'll have your quantity y minus a, in this case it's minus a -2, okay? And that's going to end up being y plus 2, but I'll change that in a moment. So this is squared, and this equals the radius, which is a, being squared. So you'd have -2 being squared, okay? So this ends up being x squared plus, you'd have y plus 2, okay? Quantity squared is equal to 4, okay? So that's converting it over to rectangular using our little formula. Now, if you don't want to do this or you're not comfortable with this, again, it's fine. It's no big deal. You can always do this the long way, okay? So for this one, I would multiply both sides by r. So you get r squared is equal to -4, and then times r times the sine of theta. If you have r times sine of theta, that's y, okay? So just go ahead and replace that with y. replace r squared. I'm not going to have room for this, but you want to replace r squared with x squared plus y squared. So this is x squared plus y squared. And again, you're just going to move things over and complete the square. That's all you need to do. So this is x squared plus, I'm going to go ahead and say this is y squared, and then I'm going to add 4y to both sides, okay? And I'm also going to leave a space here, and I'll put equals 0, right, because I added 4y to both sides. So here I need to cut 4 in half, so that'd be 2, and then square it, I get back to 4. Now because I added it over here, I've got to add it over here, so this equation becomes this. So you get rid of all this, okay? So I'm going to go ahead and say this is x squared plus, if you factor this, this is going to be y plus 2, quantity squared, and then this equals 4, okay? So this equals 4. So it's not that bad overall if you're really good with going through the steps on this. I like to use the formula. If I see something immediately, it's just a lot quicker for me. But if you want to guard against errors, this is a surefire way to do it every time. So let's think about graphing this now. Again, what I want to do is get some points. So I'm going to put r and then theta. So the first one that I'm going to do, again, I always do 0 degrees. So I know that the sine of 0 degrees is 0. So negative 4 times 0 is 0, okay? And then if I did, let's say, the sine of 90 degrees, well, I know that's going to be 1, okay? So if sine of 90 degrees is 1, then r would be negative 4. Now, if you want to convert that over, you could do positive 4 and 270 degrees if you wanted to, okay? It's a little bit easier to work with. Now, let's think about some other things. Where is sine equal to a half? Because if this was a half and I multiplied it by negative 4, better yet, if it was negative a half and I multiplied it by negative 4, I would get positive 2, okay? So sine is 1/2 at 30 degrees or 150 degrees. If you want it to be negative 1/2, then you would want to do 210 degrees, okay? That would have a 30-degree reference angle. Or you would also want to do 330 degrees. That would have a 30-degree reference angle as well. So in each case, sine of those, sine of 210 degrees or sine of 330 degrees would be negative 1/2. Negative 4 times negative 1/2 would give you 2 in each case. Okay, so let's write these out. We have 0, 0 degrees. We have 4, 270 degrees. We have 2, 210 degrees. And we have 2, 330 degrees. Okay, so let's grab these guys. So 0, 0 degrees, that's obviously at the pole. So let's go ahead and highlight that. Then 4, 270 degrees, go out to a circle with a radius of 4. We're going to swing around, okay, to 270 degrees. So that's going to be right there. We have 2, 210 degrees. So let's go out to a circle with a radius of 2. We're going to swing around to 210 degrees. So it's going to be right there. And then 2, 330 degrees, go out to a circle with a radius of 2. And then we're going to swing around to 330 degrees, which is going to be right there, okay? So again, if I have 4 points, that's enough for me to come through here and sketch that guy as a circle. Okay, let's look at another example. So we have x squared plus the quantity y minus 4 squared equals 16. Again, if you're going to use this formula, make sure it matches up. So x squared plus, you have y minus a being squared is equal to a squared. So you've got to look at this guy and this guy, right? So is this guy being squared giving you this guy? In this case, a is 4, right? Not negative 4. You're taking this right here. It's minus whatever this is. So a is 4. If I squared 4, would I get 16? Yes. If this was 17 or 18 or 19 or 20 or something that was not 16, then you could not use this formula because it does not work, okay? So this guy is going to give you the circle that passes through the origin and it's centered on the y-axis. Again, this converts over to r is equal to 2 multiplied by a times the sine of theta, okay? So if I know a is 4, then r is equal to 2 times 4, which is 8, times the sine of theta, okay? So if you know the formula, and you get these a lot, these are very common problems, you can convert them almost right away, okay? So let me erase this, and again, I'll show you how to do this the long way. So what I would do is expand this. So I'd say x squared plus y squared, and then you'd have minus 2 times this guy times this guy. So 2 times 4 is 8, and then times y, and then plus 4 squared is 16, is equal to 16. You'll notice that, again, this is going to cancel. So what you have here is x squared plus y squared, which is r squared. And then I'm going to say is equal to, I'm going to add 8y to both sides. And then y I can always replace with r. Okay, I can always replace with r times the sine of theta, okay? And again, I can just divide both sides by r. You get r is equal to 8 times the sine of theta, okay? So pretty quick to do that way as well, but the formula is actually faster, okay? So let's go ahead and get rid of this. And let me write this a little bit more neatly. So r equals 8 times the sine of theta, Okay, so let me go ahead and make that theta a little bit better. Let me go ahead and get some points for us. So r and then theta. Okay, so we know, again, if I choose a 0 here, so 0 degrees, sine of 0 degrees is 0, so this would be 0, okay? If I choose 90 degrees, well, the sine of 90 degrees is 1, so r would be 8, okay? And then I'm also going to deal with a half. Sine of 30 degrees is a half. So if I put 30 degrees here, that's a half. A half times 8 is 4. And then if I did 150 degrees, sine of 150 degrees is also a half. 8 times a half is 4, okay? So my points here would be 0, 0 degrees, and then 8, 90 degrees, and then 4, 30 degrees, and then 4, 150 degrees. So let me grab this real quick, and let's go ahead and paste this in. So 0, 0 degrees is going to be right there. If you want 8, 90 degrees, so we're going to go out to a circle with a radius. We have 1, 2, 3, 4, 5, 6, 7, and then 8. And then I'm going to swing around to 90 degrees, so it's going to be right there. And then I want 4, 30 degrees, so a circle with a radius of 4. And then I'm going to go to this angle here at 30 degrees. And then 4, 150 degrees, go out to a circle with a radius of 4. I'm going to swing around to 150 degrees, so right there. Okay, so again, 4 points is usually enough. If you need more, you can approximate some of these other ones that are not going to be whole numbers in terms of the r values, but you can get very close to where you can sketch an accurate graph. All right, so let's wrap up the lesson and look at some examples where we're not centered on the x-axis, we're not centered on the y-axis, but we're still going to have our circle pass through the origin. So to set this up, I'm going to be working with rectangular coordinates. And so let me write this out. We have x minus h quantity squared plus we have y minus k quantity squared equals r squared. So this is back to basic algebra. I'm going to be replacing things. We can see that this passes through the origin, okay, which is the point in rectangular as 0, 0. And we can see that the center, okay, right here, is labeled with rectangular coordinates a, b. So the x location is going to be a. So I can erase this and put an a. And the y location is going to be a b, so I can erase this and put a b, okay? Now, again, you've seen me throughout the lesson replace this typical r that we see in algebra for the radius with a, because we don't want to get it confused with the r that comes up in polar form. So for right now, I'm just going to erase this all together, and I'm just going to put a blank here in squared, okay? So what would I need? Remember, the radius is the distance from the center to any point on that circle. So the distance from right here to right here can be found with the distance formula if you want to use that. So you could say the distance between these 2 points would be the square root of what? Well, you would subtract a minus 0, right? You subtract the x coordinates. So let's say a minus 0 would just be a, and you're going to square that. Then plus, you're going to subtract the y coordinates. So b minus 0 would just be b, and that would be squared, okay? Now, if I put this in here and squared it, I would just get a squared plus b squared. So let me erase this and just put a squared plus b squared, okay? So that's really all there is to this formula when you see it in rectangular form. When you convert it over into polar form, it actually works out quite nicely. So let's grab this guy real quick. Let's copy it, and let's paste it on this fresh sheet here. Let's see what we can do. All right, so from here, what I'm going to do is put this into polar form. We're going to find this is really, really useful when we're trying to convert back and forth between the two. So I'm going to start by expanding this guy and this guy on the left-hand side. So we already know how to do this. This is x squared minus 2 times this guy, so minus 2ax. Then plus this guy squared, so a squared. Then plus, same thing over here, so y squared minus 2 times this guy, so minus 2 times by. Then plus this last guy, b squared. And this equals a squared plus b squared, okay? So we can see that this is on each side, right? So I can subtract it away from each side, and it's going to go away from each side. This is on each side, so I can subtract it away from each side. It's going to go away from each side. Because everything is gone on the right-hand side, I'm going to put a 0 there, okay? So over here, what I can do now is rearrange things. So I'm going to put the x squared plus the y squared next to each other. Again, that's a common theme when you're working with these problems. You're trying to get the polar. So I'm going to say x squared plus y squared. Again, you can replace that with r squared. Then what I'm going to do is I'm going to take this guy and move it over here. And I'm going to move this guy over here as well. So let me put my equals here. I'm going to add 2ax to both sides. So of course it's going to cancel over here. And then I'm going to add 2by to both sides. So again, of course, it's going to cancel over here. Okay, so this is my equation now. And basically, to convert it over to polar, x squared plus y squared is r squared by definition. And then everywhere I see an x, I can always put r cosine theta. So I'll put 2a times r cosine of theta, and then plus 2b. Everywhere I see a y, I can put r, and then sine of theta, okay? Let me erase all this. And essentially what you want to do here is solve this for r. Again, the common mistake is to take the square root of each side. What you want to actually do is factor this r out, okay? So factor this r out so that you can divide both sides by r. So I'll say this is 2a times the cosine of theta, and then plus 2b times the sine of theta, okay? And this equals the r squared, okay? So again, the trick here is I'm going to divide both sides by r. This is just multiplication here, so this is perfectly legal. Cancel one of these with this, cancel this with this, okay? And what I'm left with, let me just write this above here, okay, because we're going to use this. We'll say in polar form, this is r is equal to, you'll have your 2a times the cosine of theta, okay? And then plus your 2b times your sine of theta. So there will be a lot of problems that deal with this, both in pre-calculus and in calculus. Again, this is for a very specific case. Your circle is going through the origin, okay? And then your center is not on the x-axis, it's not on the y-axis. The center, let me write this again. So the center is going to be at a comma b, okay? And then you want to check that your radius, again, is the square root of a squared plus b squared, okay? So if your circle fits this description, okay, in rectangular, then you can quickly convert it over to polar using this form here, okay? So you take your a from here and your b from here. You can check that a squared plus b squared is what you've got here as your number, okay? And then you can convert it over. All right, let's take a look at an example. So we have r is equal to 6 times the cosine of, we have this theta plus pi over 3, okay? So the first thing I would do here is just simplify this using my cosine sum identity, okay? So I'm going to say r is equal to, I'm going to put 6. You can use parentheses or brackets, whatever you want. But basically you want to expand this out. So I'm going to say this is the cosine of theta, and then times the cosine of pi over 3. And then remember, when you use the cosine sum identity, your signs are going to change. This is plus, so it's going to be minus. So this is now going to be the sine of this theta, and then times the sine of pi over 3. Okay, close these brackets down. We know pi over 3 is 60 degrees, and cosine of 60 degrees is a half. We know sine of pi over 3, or sine of 60 degrees, is square root of 3 over 2. So let's just replace that real quick. I'll say r is equal to 6. Open up the brackets. I'll say 1/2 times the cosine of theta, and then minus, I'll say square root of 3 over 2 times the sine of theta. Okay? Now, when you distribute the 6 into each, you have a denominator of 2. 6 divided by 2 is 3. So you'd basically have 3 times cosine of theta, and then you'd have negative 3 times square root of 3 times sine of theta. Okay? So let's go ahead and say we have r is equal to, again, this would be 3 times cosine of theta, and then minus 3 times square root of 3 times the sine of theta. Okay? So here's where we can stop. I'm just going to erase all of this. We don't need it anymore. All right, so to use the formula, let's just write r equals our 2a times the cosine of theta, then plus the 2b times the sine of theta. This converts over to x minus a, quantity squared, plus y minus b, quantity squared, is equal to a squared plus b squared, okay? So if I'm trying to convert this over, here I know that 2a, I just got to match these things up, 2a is equal to 3, and 2b, okay, is going to be equal to the negative of 3 times square root of 3, okay? So be very, very careful there, because depending on your book, you might get different formulas. So I'm going to say that 2a is equal to 3, divide both sides by 2, and a is equal to 3/2, okay? So that would get plugged in here and here, okay? So let me erase this, and actually I'm just going to put this up here. So a is equal to 3/2. And then similarly, if I have 2b is equal to negative 3 times square root of 3, we'll divide both sides by 2, and b would be equal to the negative of 3 times square root of 3 over 2, okay? Let me make this 3 a little bit better, okay? And then again, you're just plugging in. So if I took that and I plugged in here, so x minus 3/2, this quantity would be squared. And make these parentheses a little bit larger. Then plus, you would go y minus the negative is plus positive, so y plus, I'll go ahead and say 3 times square root of 3 over 2, quantity squared is equal to, so you've got a square a, you've got a square b, and then you want to sum those results. So a squared, 3/2 squared, is going to be 9/4. Then plus, if you square this guy, the negative becomes positive. 3 squared is 9, square root of 3 squared is 3, and 2 squared is 4. So basically this is 27 fourths. If you add these guys together, because you do have a common denominator, you're going to get 36 over 4, which is 9, okay? So this right here would be how you can quickly convert, and I say quickly, but how you can more quickly convert this over to your rectangular form. I realize this problem does take some time, no matter how you do it, okay? So what I would do from here, let me just erase this, and I'm just going to do this the long way. Okay, so when you see something like this and you're trying to convert it to rectangular, remember, r squared is x squared plus y squared, and if you have r times cosine of theta, it's x, and r times sine of theta, it's y. So the strategy here, if you just have r, is to multiply both sides by r. This would give me r squared is equal to 3r cosine of theta minus 3 times square root of 3 times r times the sine of theta. Okay, I just multiplied both sides by r. Now I can replace things. So this is x squared plus y squared, okay? And this equals, this is going to be 3x, and then minus, this is going to be 3 times square root of 3, and then times y. Now, if you feel more comfortable, you can write the y right here. So you could also write this as negative 3 times y times square root of 3. A lot of books will do this so that you don't get confused and think that the y is underneath the radical there. So we'll just kind of use this notation, but the coefficient for y is negative 3 times square root of 3. So we have to know that. Okay, so what I want to do now is move things over. So I want to move these guys over here, okay? And the reason I'm going to do that is so that I can complete the square. So if I subtract 3x away from both sides, I'm going to have x squared. I'm going to have minus 3x. Then I'm going to put plus, and I'm going to leave a space, right? Because I want to complete the square. Then plus, I'm going to have my y squared. I'm going to add this to both sides. So plus 3y times square root of 3, okay? Then plus, I'm going to leave a space. And this equals, I'm going to put 0. So what I would do here is complete my square. Again, take the coefficient for your variable raised to the first power. So in this case, it's negative 3. Cut it in half, so that would be negative 3 halves. Square it, you would get 9 fourths. Okay, so let me write 9 fourths here. Again, it's not legal to do this unless you add it to both sides. So we got to put it over there. Okay, then over here, this one is a little bit more tricky, but we just did it. It's 3 times square root of 3. Cut it in half, and I'm writing these 3's terribly. So let me put this in a little bit better form here. Cut it in half and then square it. We just saw this was going to be 27 fourths. So this is 27 over 4. Okay, so plus 27 fourths. We already know this becomes 36 fourths, and this is 9, right? Because we basically just did this. So this is 9, okay? And again, if you go through and factor these, this is a perfect square trinomial, and this is a perfect square trinomial. So this factors into x minus your 3 halves quantity squared. And then plus, this is going to factor into y plus your 3 times your square root of 3 over 2, quantity squared, and this equals 9. So however you do this, you're going to get the same answer. I just want to give you multiple ways to attack the same problem. Okay, let's erase all this. In order to graph this on the polar grid, I'm going to use this form. It's a little bit easier when you just have cosine involved versus having cosine and sine, because I can just plug stuff in here, then add the 60 degrees to it, and then I can take the cosine of that, so on and so forth. So I'll say r and then theta here. I've got to think about the fact that whatever I plug in there, I'm adding 60 degrees to it. So if I put in 0 degrees, I add 60 degrees to that, I get 60 degrees. Cosine of 60 degrees is a half. A half times 6 is 3. Then if I did something like, let's say, 30 degrees, well, if I add that to 60 degrees, I have 90 degrees. Cosine of 90 degrees is 0. 0 times 6 is 0. Let's keep going with 2 more points. Again, I'm just trying to get some whole numbers here. So let me also do something like 240 degrees. 240 degrees plus 60 degrees would be 300 degrees. That has a 60-degree reference angle, right? And it's also in quadrant 4, so it's going to be positive. So the cosine of 300 degrees is a half. 6 times a half, we already know, is going to be 3, right? So if this was 240 degrees, okay, again, adding 60 degrees gives me 300 degrees. Cosine of 300 degrees is a half. 6 times a half is 3. All right, the last thing I want to consider, we know that the cosine of 0 degrees is 1, okay? But again, I'm adding 60 degrees to this. So let me go ahead and put 300 degrees in here. Okay, that's another one we can try. So 300 degrees plus 60 degrees would be 360 degrees. Cosine of 360 degrees is the same as cosine of 0 degrees. It's going to be 1. So 6 times 1 would just be 6. Okay, so this is 4 points. Again, if you need more, you can always use some approximations. I'm going to go ahead and say 3, 0 degrees. I'm going to say 0, 30 degrees. I'm going to say 3, 240 degrees. And then I'm going to say 6, 300 degrees like this. I'm I'm going to grab these guys, copy them. Let's paste this in here like that so we have it. So again, 3, 0 degrees, well, basically from the pole, I'm just going to step out to a circle with a radius of 3. So I'm just going straight to the right like that. And then 0, 30 degrees, again, if this is 0 here for the radius, I'm not going anywhere, right? So I'm going to be right there on the pole. 3, 240 degrees, I'm going to step out to a circle with a radius of 3, swing around here to 240 degrees, so it's going to be right there. And then you have 6, 300 degrees, so I'm going to go out to a circle with a radius of 6. I'm going to swing around to an angle of 300 degrees. Let's go right there. So again, if you need some points in between these to make a more accurate sketch, you can use some approximations. Okay, that's up to you. Generally speaking, if you do this for a homework assignment and you show 4 points and you draw your circle through those points, you're pretty much good to go. All right, so the last example here that we're going to do, we have x plus 3 quantity squared plus we have y plus 1 quantity squared equals 10. So for this, again, I'm going to write this in the form of x minus a quantity squared plus we have y minus b quantity squared is equal to a squared plus b squared. So you first want to check to see if this matches up. So if you have plus some number, you have it here and then here, right is minus a negative. So I'll say x minus a negative 3, and then quantity squared, plus you have y minus a negative 1, quantity squared is equal to, in this case you'd have negative 3 being squared, so negative 3 being squared, plus you'd have negative 1 being squared. So first you want to check to make sure that this works out. If this was, let's say, 11, you could not use this formula because it doesn't work out. Negative 3 squared is 9, negative 1 squared is 1, 9 plus 1 is 10, not 11, right? Or if it was 12 or 14 or anything other than 10, this is not going to work out. But since it does follow this format, what I can do is just grab these values so I can say this is A, and I can say this is B, and then you can just plug in, right? So you can say R is equal to, well, I have 2 times A, so 2 times negative 3, times the cosine of theta. Then plus, I have my 2 times b is negative 1, times the sine of theta. Okay, and that's all you need to do. So let's come down a little bit. So this would be r is equal to, we'll have 2 times negative 3, which is negative 6, times the cosine of theta. Then we'll have 2 times negative 1, which is negative 2. So I'll just put minus 2, and then times the sine of theta. Okay, so this is converted into polar form. Again, just for the sake of completeness, I'm going to do this one more time the long way, just so you get some practice. If I come back up here and I expand this, this is x squared plus 2 times this guy, so 6x plus this guy squared, so 9, plus this guy is y squared, plus 2 times this guy, so 2y, plus this guy squared, which is 1, and this equals 10, okay? So if you sum 9 and 1, you get 10, and again, you can subtract that away from each side. So I'm going to go ahead and line these out, and line this out, and put a 0, right? Just like I subtracted 10 away from each side. So then from here, what I'm going to do is do my x squared plus y squared. I'll just go ahead and say that's r squared. And I'm going to say this equals, I'm going to move these guys over to the right-hand side. So I'm going to subtract 6x away from each side, and I'm going to subtract 2y away from each side. So then I'll have r squared is equal to negative 6 times, this is r cosine of theta, then minus 2 times, this is r sine of theta, okay? And then from there, again, you can always factor the r out. So you have it here, and you have it here. So let me write r squared is equal to r times the quantity, negative 6 times the cosine of theta, then minus 2 times the sine of theta, okay? And then let me divide both sides by r. So divide both sides by r. And one of these will cancel with this will cancel with this, and you're back to that form that we found. So r is equal to negative 6 times the cosine of theta, then minus 2 times the sine of theta. All right, so graphing this guy is a little bit more challenging. Even if you were on the rectangular coordinate plane, you would basically graph the center, which would be at negative 3, negative 1, and then you would move up by square root of 10 units. You would move to the right by square root of 10 units. You'd move to the left by square root of 10 units, and you move down by the square root of 10 units. That would give you your 4 points on the circle, and then you could sketch your circle. But here, because 10 is not a perfect square, we're going to have to do a lot of estimation. Let me go ahead and put my r and my theta. And I'm going to first start with 180 degrees. And the reason for that is I want something that's going to cancel this out completely, and I want something that's going to multiply by this negative 6 and be negative 1. So the cosine of 0 degrees is going to be 1, but the cosine of 180 degrees, because we're flipped over now, we're going to be at negative 1, okay? So if I plugged in 180 degrees there for theta, this is gone, that's 0, right? And then this right here would be negative 6 times negative 1, which is 6. So that's one whole number value that we can get. So let me put 6, 180 degrees. And then another one that we can get, if we do 270 degrees, the cosine of 270 degrees, that's going to be 0, so this will be gone. And the sine of 270 degrees is -1, so -2 times -1 is 2. So if I do 270 degrees, then basically I would have 2. Now for the other points, let me go ahead and put this down here as 2, 270 degrees. I'm going to go ahead and approximate some stuff. So again, you just got to pull your calculator out. I'm going to go with 135 degrees. I think this one's going to be a little bit easy for us to work with. So if you plug this in here and here, and you punch that into your calculator, you're going to get 2 times square root of 2. So 2 times square root of 2. Okay, so 2 times square root of 2. And this is 135 degrees. If you want an approximation for that, you could say 2 times square root of 2 is approximately 2 point, let's just go ahead and say 83. Okay, so that's close enough for me. Maybe you want to get something that's a little bit closer, so you can just include more decimal places. Now let me get one more guy going here. Again, you take as many as you need. I'm going to go ahead and go 210 degrees here. That works out kind of nicely. So if I punch this into my calculator, I'm going to end up with 3 times square root of 3, then plus 1. Okay, so 3 times square root of 3 plus 1, and then 210 degrees. Okay, so this one, let me go ahead and write this over here. I think I'm going to run out of room, but I'll just put it right here. So 3 times square root of 3 plus 1 is approximately, let's go ahead and say 6.2. Okay, so I'll say 6.2. So let me grab these guys real quick. I'm going to copy this, and let's come over here. I'll paste this in. Again, I've already drawn this with a computer, which nowadays pretty much everyone does that. So I'm just going to go ahead and plot these the best that I can. So 6, 180 degrees. So I'm going to go out to a circle with a radius of 6 and then swing around to 180 degrees. So it's going to be right there. And then 2, 270 degrees. Go out to a circle with a radius of 2. I'm going to swing around to 270 degrees. So it's going to be right there. And then 2 times square root of 2, we said was about 2.83. Okay. So 2.83. So let me come out to about right there, I'd say, and then swing around to 135 degrees. That's going to put us about, let's just say right there. Again, you can't get this perfectly. We're just trying to sketch a circle, get an idea of what this looks like. If you need something perfect, you can use your TI-83 or 84, or you can use a graphing calculator online. Then we have 3 times square root of 3 plus 1. We said that was about 6.2. So let's go out to this about 6.2 right here. And then we said that it was 210 degrees. So let me swing this around to 210 degrees. So that's going to be about right there. Okay. So from those points, again, you could sketch your circle. It won't be perfect, but it'll be close enough to get your assignment completed. In this lesson, we want to talk about the inclination of a line, the angle between two lines, and also the distance between a point and a line. All right, so what I want to do is start out by talking about the angle of inclination. So I'm going to go through a few scenarios with you generically, and then we'll look at some examples. So this is what you'll probably see in your textbook, and there's just a few things to go through here. Essentially, every non-horizontal line is going to impact the x-axis somewhere. So in this case, we're looking at a positively sloped line, okay, and it's going to impact our x-axis right there. Okay, so we're saying the point is x sub 1, that's your x value, and then 0 for the y value because, again, it's on the x-axis. You can label this as y sub 1. We're going to need that in a moment. Now, when we talk about this angle of inclination, we're considering the angle formed from the x-axis here, okay, measured counterclockwise to this line. So we're going to name this with theta. Okay, so that's going to be our angle. So with this guy right here, the first thing is I would consider the slope of this line. So remember, if we have 2 points in a line, so we have this point and then we have this point, we can use our slope formula. So m, which is classically used to denote slope, is equal to, remember, it's rise over run. So typically we see y sub 2 minus y sub 1 over your x sub 2 minus your x sub 1. Okay. Now, in this case, we know that y sub 1 has a value of 0, so you can just plug that in, okay? And then essentially, you can simplify this. In this particular case, let me make this a little bit neater. I'm going to say that m, our slope, is going to be y sub 2 over x sub 2 minus x sub 1. Okay, so that's pretty easy to understand. Now, the other thing we can consider here is that we could form a right triangle, okay? So what I'm going to do is have this side right here, and the length of this side, which is adjacent to our angle theta, is going to be x sub 2 minus x sub 1. So this x-coordinate here, whatever it is, minus this x-coordinate here, whatever it is, would be the length of this side. Then let's do the opposite side as well. So this is opposite of our angle theta. And this guy has a length of y sub 2, whatever that is, because you have y sub 2 minus your 0 there, because this point right here, again, is on the x-axis. So I want you to notice that the tangent of theta is equal to what? Well, it's opposite over adjacent. So this is y sub 2 over x sub 2 minus x sub 1, okay? So do you see the relationship between the slope of the line and the tangent of theta? Well, they're going to be equal, right? M, the slope, is equal to the tangent of theta because they both have the same definition here. So I can say that M, our slope, is equal to the tangent of theta, okay? But like all things in trigonometry, it's not always so straightforward to get your answer. All right, let's start out with the easiest scenario. This is where you have a positively sloped line, like we just looked at. Here you're going to have an acute angle for theta. Okay, so your angle of inclination will be greater than 0 degrees and less than 90 degrees. So in this case, you can just plug straight into your inverse tangent function. Okay, so if you have a positively sloped line, that's all you need to do, you'll have the correct answer. Okay, now the harder scenario occurs when basically you have a negatively sloped line like we see here. So now you're going to have an obtuse angle. So theta is going to be greater than 90 degrees and less than 180 degrees. And for this guy, you have to do more work because when you use your inverse tangent function, basically you're going to get something in quadrant 4. It's going to rotate clockwise like this, and you're going to get this angle measured clockwise, okay? So what you're going to have to do is you're going to have to take that angle you get and add it to 180 degrees so that you can get this obtuse angle here that's going to be in quadrant 2. Some other special case scenarios, obviously you'll have a horizontal line and a vertical line. You should know that basically if you have a slope of 0, right, something like y is equal to k, that's a horizontal line, the slope is 0, so theta there is just going to be 0 degrees. Now lastly, you could also get a vertical line. We know theta here, you're basically going to have a right angle, so theta there is going to be 90 degrees, and we know the tangent of 90 degrees is not defined, right? We know that with a vertical line, something like x is equal to k, you have an undefined slope. With all of that being said, let's go ahead and look at an example. So what I'm going to do is take this 4x plus 5y equals 20 and put it in the slope-intercept form. So y equals m the slope times x plus b the y-intercept. And so I'm going to subtract 4x away from each side of the equation. That would cancel. I'll have my 5y is equal to negative 4x plus 20. Divide everything here by 5. And this is going to give me that y is equal to, we'll have negative 4/5, okay, that's going to be my slope, times x and then plus 4, okay? Now, a lot of times when you first start doing these, you might want to graph it just to understand what's going on. But essentially, you know that if you have a negative slope, which we have here, m is negative 4/5, that essentially you have an obtuse angle, right? So you have to do additional work with this guy. And to verify that, let's just look at the graph real quick. So the slope is negative 4/5 and the y-intercept is going to be at 0, 4. So let's look at the graph. So my y-intercept, again, is at 0, 4, so that's there. And my slope is negative 4/5. So drop 1, 2, 3, 4 to the right, 1, 2, 3, 4, 5. That will give you that point right there, okay? So we're looking at this angle right here, theta, and we're trying to figure out what that guy is. You can see just by inspection that this guy is going to be an obtuse angle, okay? So we know we're going to be in quadrant 2. So again, what you want to do is you want to say the tangent inverse of this guy, so negative 4/5. Just punch that into your calculator. You're going to get approximately, I'd say, negative 38.66, okay? And let me put degrees there to be specific. Now, once you have this, again, what you want to do, because you're looking for your angle in quadrant 2, this is giving you something in quadrant 4 rotating clockwise, okay? So what I want to do is I want to say, okay, 180 degrees plus this negative 38.66 degrees is going to give me, I'll say, about 141.34 degrees, okay? So this would be my angle of inclination. Obviously, this is an approximation, and I'll say theta is approximately 141.34 degrees. Now, what I would do when I first start this is go back to your picture if you made a graph and just say, okay, is that about 141.34 degrees? Yeah, that looks about right. So I'm going to put approximately 141.34 degrees. All right, let's try another one. So we have negative 2x plus 3y equals 6. Again, I'm going to put this in slope-intercept form. So y equals mx plus b. So basically I would have, if I add 2x to both sides, then what I would have is this canceling over here. I'll have 3y is equal to 2x plus 6. And then I'm going to divide both sides by 3, okay? And I'll have y is equal to 2/3, okay, that's going to be my slope, times x plus 6 divided by 3 is 2, okay? So your slope, let me get rid of this, your slope m is going to be 2/3, and your y-intercept is going to occur at 0, 2, okay? So if we look at the graph of this guy, you would say, okay, well, your y-intercept is at 0, 2, your slope is 2/3. So up 1, 2, to the right, 1, 2, 3. Okay, so right there. Up 1, 2, to the right, 1, 2, 3, so right there. Okay, so you have some points, you can draw that line. Again, we're looking for this angle theta. You can see this is an acute angle, right? So basically, I would want to say the tangent inverse of, let's go ahead and say 2/3. This is approximately, I'll say 33.69 degrees. And we don't need to do anything else here because this guy is in quadrant 1, right? So basically I can say this is approximately 33.69 degrees. If you want to go back to where we had our problem, you could say theta, again, is approximately 33.69 degrees. So when you have a positively sloped line like this, it's really, really easy. Just plug this into your inverse tangent function and you're done. You don't have to do any extra work. Okay, let's look at one that is in reverse. So now we're given our angle of inclination. Our theta is 135 degrees, and we're given a point on the line, which is -7, 2. And essentially we want to write the equation of the line. And so if we wanted to do this, the first thing is we need to figure out the slope, right? So the slope is going to be what? Remember, m is equal to the tangent of theta. Well, I have theta, so if I take the tangent of 135 degrees, what would that give me? So my tangent of 135 degrees is equal to, I'll go ahead and say m, which is equal to -1, okay? So I know the slope is -1, so let me erase this and put -1 here. You can get rid of this. Now, if I have my slope, which in this case is -1, and I have a point on the line, let's call this x1 and then y1, well, I can plug into something called point slope, right? So y minus y1 is equal to m times the quantity x minus x1. So here, y minus my y1 is 2, is equal to m, which is -1, times the quantity x minus x1 is -7, minus the -7 is +7. Now you can solve this for y and put it in slope-intercept form. You might also be asked to put it in standard form, so just get with your instructions. So y minus 2 is equal to, this would be -x, and then -7. Let me add 2 to both sides of the equation. Let me erase this, and I'll go ahead and say that our equation is y is equal to, we'll say that it's -x, and then we'll go ahead and say -5. Okay, so that's your slope-intercept form of the line. If you want to look at this graphically, your y-intercept would occur at 0, -5, and your slope would be -1. So your y-intercept would be at 0, -5, so that's right there, and your slope is -1. So if you wanted to get points going this way, you would go up 1 into the left 1, 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 till you get to this point here, and you can see we have this angle theta here, which is going to be equal to 135 degrees. All right, so what we want to do now is talk about the angle between two lines. So if you have two lines in a plane, they're either going to be parallel lines, in which case they'll never intersect, or they'll be non-parallel lines, and in that case, they will intersect at some point, okay? So the case we would talk about here today will be non-parallel lines, obviously, because we need some point of intersection, and also they're not going to be perpendicular lines because we don't want them to meet at 90-degree angles, okay? So we're talking about the other situation. So I have a little image here, which I want to focus on. So you'll see that this point of intersection here forms two pairs of opposite angles. So you have these acute angles. So you have this one and you have this one, right? So those would have the same measure. And then you have these obtuse angles. So you have this one and then you have this one, right? So those would be of the same measure as well. What we're going to focus on when we say the angle between two lines, we're focused on this acute angle right here, which I'm calling theta, okay? So we're going to be focused on how to find theta. So theta is equal to what? Well, to come up with a little formula, we're going to start off with this scenario, and this won't work in every scenario, so we're going to have to adjust our formula just a little bit, okay? So we're going to say that this blue line here is a negatively sloped line, okay? And so the angle of inclination here, theta sub 2, we know that that would be an obtuse angle, right? So we can say that theta sub 2 is greater than 90 degrees and less than 180 degrees. So we know this. Then this orange line is positively sloped. So we know theta sub 1, the angle of inclination there, is an acute angle. So theta sub 1 is greater than 0 degrees and less than 90 degrees. So based on this, we know that theta sub 1, in this case, is going to be less than theta sub 2, okay? So we can say, let me erase this, I'll just say that theta sub 1 is less than theta sub 2. Okay, so that's for this case. Now another thing we can say, because these lines are not going to be perpendicular, I can say that theta sub 2, which is the bigger angle here, minus theta sub 1, which is the smaller angle, is going to be strictly less than 90 degrees. Because if this was equal to 90 degrees, these guys would be perpendicular, okay? So we're talking about these two assumptions to make what I'm about to say work. If these two assumptions don't hold, we're just going to change our formula up just a little bit. We're going to do this with using the absolute value operation, but we'll get to that later on, okay? So what I'm going to say here is that if I want this angle here, okay, I can find it by first getting this larger angle, okay, think about that, and then just subtracting away the smaller angle. So in other words, I'm just finding this piece right here. So it's going to be the theta sub 2, okay, minus the theta sub 1. So this is equal to, we'll say theta sub 2 minus theta sub 1, okay? So that's for this case right here. We're going to use this to derive a little simple formula, and then I'll show you how to correct it for other scenarios, okay? So let's go down and say that we have theta is equal to theta sub 2, remember this was our bigger angle, minus our theta sub 1, which was the smaller angle, okay? So what we're going to do here is we're going to take the tangent of each side. So I'm going to say the tangent of theta is equal to, we're going to say the tangent of this theta sub 2 minus this theta sub 1. Remember, you cannot distribute this in, you have to use an identity. So if we go back to our sum and difference identities, we see the tangent of A minus B is the tangent of A minus the tangent of B over 1 plus the tangent of A times the tangent of B, okay? So we're just going to follow that. And we're going to say that this is basically equal to, we'll do the tangent of this first guy, theta sub 2, minus the tangent of this second guy, theta sub 1. This is over, we're going to do 1 plus, we're going to multiply the two together. Now, your book is going to usually change the order of this. This is up to you. So I'm going to go tangent of theta sub 1 times the tangent of theta sub 2, okay? With your identity handout, it's tangent of theta sub 2 times tangent of theta sub 1, but you can multiply in any order, you'll get the same answer, so it doesn't matter, okay? So let's go down a little bit. We're going to keep this going. From here, I'm going to make some other substitutions. I want you to recall that we say that our slope of a line, m, is equal to the tangent of our angle of inclination, which we call theta, okay? So now let's say I have two different lines, so I have two different slopes and two different angles of inclination, okay? So I'm going to say that this is m sub 1, and this is going to be theta sub 1, and this is m sub 2, and this is going to be theta sub 2. So what I'm going to do now is just plug some things in. Since m sub 1 is equal to tangent of theta sub 1, well, where I see a tangent of theta sub 1, I can just plug in an m sub 1. And then similarly, wherever I see a tangent of theta sub 2, so here and here, I can just plug in my m sub 2. Okay, so that's all I need to do. So let me slide this over a little bit so I can fit everything on the screen. I'm going to say that this is my m sub 2, and then minus my m sub 1, okay? And then over 1 plus, I'm going to multiply them together, so m sub 1 times m sub 2, okay? So let's talk about correcting this. Essentially, because I want to end up with an acute angle, okay, and I don't want to have to worry about which slope is going to get put as m sub 1 or which slope is going to get put as m sub 2, I can just use absolute value bars here, okay? The reason this works is that basically if you do this in the wrong order, you're going to end up with a negative inside of here, okay? And so you don't want that, right? Remember, if you do the inverse tangent with a negative, you're going to get something in quadrant 4, okay? If you add 180 degrees to that, you're going to get the obtuse angle that's between these guys, and you want the acute one, okay? So you just want to make sure you use the absolute value bars so that whatever answer you get, just make it positive, okay? And when you make it positive, when you do your inverse tangent function, you're going to end up with the answer in quadrant 1, which is your acute angle between the lines. All right, so we have 3x minus y equals 1 and x minus 3y equals negative 6. So I like to put these in slope-intercept form. I also like to graph them. So let's go ahead and say this is going to be what? This is negative y. And then I'll say equals negative 3x plus 1. I just subtracted 3x away from both sides. And then basically I could multiply everything by negative 1. So that would change this sign, and this sign. Okay, so in slope-intercept form, this is just going to be y is equal to 3x minus 1. Then for this one, you would have negative 3y is equal to, I'm going to subtract x away from each side. So I'll have minus x over here, and then minus 6. I'm going to multiply both sides by negative 1/3. So this would cancel. If I multiply this by negative 1/3, this would be positive 1/3. And then negative 1/3 multiplied by negative 6 would be positive 6 divided by 3, which is positive 2. Okay, so this is my slope-intercept form there. So if you wanted to graph these two, this one has a y-intercept of 0, negative 1 and a slope of 3. And then this one has a y-intercept of 0, 2 and a slope of 1/3. Let me grab this real quick. Let's look at a graph real quick. Let me paste these in so we have some reference for where this stuff came from. So we have 0, negative 1, so basically right here. And the slope for this one is 3. So up 1, 2, 3 to the right 1. Okay, so there's a point there. Then up 1, 2, 3 to the right 1, so there's another point there. Okay, so that's this line right here with a slope of 3. Okay, then the other guy is going to be 0, 2. So we have this guy right here. Okay, the slope is 1/3. So up 1 to the right 1, 2, 3. So there's a point. Up 1 to the right 1, 2, 3. So there's a point right there. Okay, so you see how we get the graphs of these guys. And what's important is to understand what you're looking for. You're looking for this angle right here, this acute angle theta. Okay, now in some cases you're going to want to find this angle right here. And basically, once you've found this angle right here, you can subtract 180 degrees minus that angle. It'll give you this angle right here. So let's go back and let's think about how we can find this. I'm going to say that m sub 1 is equal to 3. I'm going to say m sub 2 is equal to 1/3. And then I'm just going to plug into the formula that I had. So I'm going to say the tangent of theta is equal to, remember, you're going to do m sub 2. Actually, I should probably write this out. So the absolute value of m sub 2 minus m sub 1. So that goes up here. And then down here, you're going to have 1 plus m sub 1 times m sub 2. Okay? So my tangent of theta is going to be equal to, we're going to do the absolute value of, let's go ahead and do 1/3, then minus 3. Okay? And then down here, I'll do 1 plus, you'll have 3 times 1/3. Okay? Can't really fit this all on the screen, so let me cut this away. Let's go to this blank sheet here and see if we can just crank this out. So this equals what? What is 1/3 minus 3? Well, you get a common denominator there. 3 would be 9/3. Basically, 1 minus 9 is negative 8. So this would be negative 8/3. Let me put my absolute value bars in there so don't forget them. And then basically down here, 3 times a third is 1. 1 plus 1 is 2. So this is divided by 2. And then what I could do here is say, okay, this is the absolute value of negative 8/3. Since I'm dividing by 2, you can think about this as 2 over 1. Just flip that guy, multiply. So times a half, okay, like this. So from here, I can cancel this 8 with this 2 and get a 4 here, okay? So this would be negative 4/3, but we're taking the absolute value, so we end up with 4/3, okay? That's important because, again, we want to get an acute angle. So when we do our inverse tangent, we want this to be positive, so we get something in quadrant 1, okay? And let's bring this up here. So tangent of theta equals 4/3. What I'd want to do is say the inverse tangent, so the inverse tangent of 4/3 is going to be equal to what? And I'll do an approximation here. I'll say this is about 53.13 degrees. Now, if you wanted the other angle, again, if you go back, this one is about, let me write this in, 53.13 degrees. Again, because this right here, okay, this angle right here would be a straight angle, all you'd have to do is take 180 degrees minus this angle here if you wanted this angle right here, okay? So if you wanted this guy right here, you would say 180 degrees minus 53.13 degrees. That would give you 126.87 approximately degrees, okay? So sometimes they'll ask you to get this one. Usually you're asked to find this one, but that's how you find both. Okay, pretty easy overall. Let's go ahead and take a look at another example. So for this one, again, I'm just going to put these in slope-intercept form. So I would say this is 4y is equal to, I'm going to subtract 3x away from each side, and I'm going to divide everything by 4. So that would give me y is equal to, I'll have negative 3/4 times x plus 3. So my slope here, my m, let's call it m sub 1, is equal to negative 3/4. And I'm going to write the y-intercept just so we can graph it and see what it looks like. Again, not necessary, so this is 0, 3. Just doing it to get a full view of what's going on. So let's erase this, and let's drag this up here. Okay, let me change my ink color. For this one, I would do what? Negative 4y is equal to, subtract x away from each side, so negative x plus 8. Divide everything by negative 4, okay? And that's going to give me that y is equal to 1/4 x. So let's put this as 1/4 x. And this would be minus 2, right? So minus 2. So m sub 2, let's say this is 1/4 here. And my y-intercept is going to occur at 0, negative 2. Again, let's copy this real quick. Let's look at the graph. So the y-intercept is at 0, 3. So that's going to be right there. And then the slope is negative 3/4. So down 1, 2, 3. To the right, 1, 2, 3, 4. So that's that point right there. Then the other guy is 0, negative 2. So just drop by 2. So that's right there. And then basically the slope is 1/4. So I can go up 1 to the right, 1, 2, 3, 4. Okay, there's a point. Then up 1 to the right, 1, 2, 3, 4. There's a point. Okay, so we see where these graphs came from. And again, what are we trying to figure out? We're trying to figure out what is this angle right here. And I'm just going to plug into my formula. So let me box this off. So the tangent of theta, again, hopefully you have this written down, is the absolute value of, you're going to do m sub 2, which is 1/4, minus m sub 1, which is negative 3/4. And I'll just leave that like that for now. I'll just simplify as I go. Then it's going to be 1 plus the product of the 2. So you'll have your negative 3/4, and then times your 1/4, okay? So 1/4 minus a negative 3/4 is like 1/4 plus 3/4. There's already a common denominator, so it's just 1 plus 3, which is 4, over 4, which is basically just going to give us 1, okay? So that part is very simple. Down here, if you multiply these together, you would end up with negative 3/16. So this down here is minus 3/16. The 1 there can be written as 16/16. And of course, if you subtract, you would get 13/16. So 13/16. Now, this is already positive, so you can go ahead and drop the absolute value bars. You don't need them. And then basically, if I take 1 and divide by this fraction, all I need to do is flip the fraction, right? So essentially, this ends up being 16/13. So 16/13. So let's punch up in our calculator tangent inverse of 16/13 and see what we get. So we get about 50 point, I'll go ahead and say 91 degrees. So if we go back, so this angle theta is about 50 point, and I'll say 91 degrees. Again, if you're looking for this angle here, okay, remember this guy right here, if you consider this as a straight line, right? So this whole thing is 180 degrees. I know we're flipped upside down, so it's a little bit hard to see. But this angle right here, if you think about it, would just be 180 degrees minus 50.91 degrees. So it would be about 129.09 degrees if you need that angle. All right, so the last concept we're going to talk about is how to find the shortest distance from some line that you're given to a point that is not on the line, okay? So what I'm going to do here is give you a simple formula that you can plug into. Instead of going through and deriving this specific formula, I'll show you how you can go through a similar thought process with our actual example. Okay, I think it's a little bit easier to comprehend. So let's say that we start with some point x sub 1 comma y sub 1, okay? And it's not on this line that we're given, which has the format of ax plus by plus c equals 0, okay? If you want the shortest distance from this point to this line, then you can plug in to our little formula here, where we say d, the distance, is equal to, you have absolute value bars on the top. You're going to need them to make sure that you get a result that's going to be positive. You can notice that your a, your b, and your c here are coming from your equation of the line, right? Here's your a, it's the coefficient for x. Here's your b, it's the coefficient for y. And here's your c, it's your constant, okay? Then when you see that down here, it's the same thing, okay? Now, when we talk about the x sub 1 and the y sub 1, this is coming from your point that you're given, okay? So let's just try this out really quickly on an example, and then I'll show you where this comes from. So let's say we're given the point 5, 3, and we're given the line y equals 3x plus 4, okay? The first thing is you want to rewrite this. You have to have this in the form of ax plus by, and then plus c is equal to 0, okay? People often make the mistake of writing this as ax plus by equals c, okay? That's what you're used to for standard form, but we need to put it into this form in order for that formula to work, okay? So what I'm going to do is I'm going to just subtract y away from each side of the equation, and so that would give me, let me line this up, 3x, and I would have minus y, and then I would have plus 4, and this equals 0, okay? So if you want to line things up, here you would say a is 3, so a is equal to 3. Then b is equal to what? You have a negative y. I could put a negative 1 there to make that clear that the coefficient is negative 1. And then c, your constant term, is going to be 4, okay? Then when we talk about the x sub 1, it's the x coordinate from the point, so that's 5. And then your y sub 1 is the y coordinate from the point, so that's 3, okay? So this is all you really need to do. Just figure out how you can put this into this format and just grab the values that you need. So now I'm just going to plug into the formula. So my distance is equal to, remember you want the absolute value bars, and then let me put this over. The bottom part's easy, so square root of a squared. So a squared plus b squared. Up here, remember you would take your a times your x sub 1 plus your b times your y sub 1 and then plus your c, okay? So that's a pretty easy thing to remember after you do it a few times. Let me go ahead and see if I can move this up, and let's go ahead and paste that right there. Let's erase that and make this border a little bit better. Okay, so if we plug in here, we'll have d is equal to the absolute value of, we have a, which is 3. Let me write this out. So 3 times your x sub 1, which is 5, and then plus your b, which is negative 1, times you're going to have your y sub 1, which is 3, and then plus your c, which is 4. Okay, close that down. And this is over the square root of, you would have a squared, so 3 squared, plus b squared, so negative 1, wrap that in parentheses, squared. Okay, scroll down and get a little bit of room going so we can work on this. So d is equal to, 3 times 5 is 15, so let me write this, 15. Negative 1 times 3 is negative 3, so minus 3. And then we'd have plus 4. Okay, so if we do 15 minus 3, that's 12. And then 12 plus 4 is going to give me 16. Okay, so you have the absolute value bars. You can wrap it in that. But this is going to be positive, so you really don't need them in this case. This is basically just going to give you positive 16 up here. Okay, then in the denominator, you have 3 squared, which is 9. And you have negative 1 squared, which is 1. So 9 plus 1 is 10. So this is the square root of 10. Okay. Now we know that we don't leave radicals in the denominator. So let me fix this by multiplying the numerator and the denominator by the square root of 10. Right. So what we'd have here is that you'd have 16 times the square root of 10 over square root of 10 times square root of 10 is 10. Now, you can simplify this further because between the numerator and denominator, you have a common factor of 2. So this divided by 2 is 8. This divided by 2 is 5. So the final answer is going to be 8 times the square root of 10 over 5. Okay, so now let me give you a little bit of insight into where this formula comes from. I'm not going to use the generic notation because every time I teach that, I find that students get lost. So using an actual example is a little bit easier to comprehend. So the first thing is, I want to think about if I want the shortest distance between this line and this point, which is not on the line, what's going to happen is I'm going to need to find, let me go to a little image here. I'm going to need to find the perpendicular line segment that's going to join this point here and this line here, okay? So what you could draw is a little line like this, okay? And I'll show you how to get this line in a moment. But basically, you're looking for the distance from this point to this point right here, okay? If you just took this part of the line, okay, that's the line segment that connects this point right here, which is the point of intersection, okay, and this point right here, which is 5, 3. That is the shortest distance from this point to this line, okay? You can see we have a little right angle that's formed because these guys are going to be perpendicular. So let's go back, having viewed this, let's think about a few things. First and foremost, perpendicular lines have slopes whose product is negative 1. So if the slope here is 3, so if my first slope m is 3, let's call this m sub 1, then m sub 2 would have to be what? We can go through and set up an equation for that, but you really don't need it. 3 times what would give me negative 1? 3 times negative 1/3, right? It's always the negative reciprocal of the number, right? So flip the number, you get 1/3. Take the negative of it, you get negative 1/3, okay? So now what I can do is I can say, okay, well, I know my slope. Let me just get rid of this. I'll just say I know my slope over here, my m, is negative 1/3. But how do I get the equation of the line? Remember, I know this point right here is on the line. So if I have a point and I have the slope, then I can use point-slope formula, okay? So I can say y minus y sub 1 is equal to m times the quantity x minus x sub 1. I know it's been a while since we used that, but basically I would plug in for x sub 1 and y sub 1. So my x sub 1 is 5. Let's plug that in. My y sub 1 is going to be 3. Plug that in. And my m, my slope, is negative 1/3. So negative 1/3, okay? So we can get rid of this. And basically from here, I can distribute this. So let's say y minus 3 is equal to negative 1/3 x, and then plus 5/3. You could solve for y by adding 3 to both sides of the equation. Let's call this 9/3 so we can have a common denominator. Let's get rid of this from over here. So I'll put y is equal to negative 1/3 x plus, this will be 14/3. Okay, so this will be 14/3. So let's come over here and say y is equal to negative 1/3 x and then plus 14/3. Okay, so now that we have that done, if we go back to the two graphs, you can see that the slope of this line is negative 1/3, right? If I started, let me erase all this, I've kind of marked it up. If I started, let's say right here, okay, which is a point on the line, if I drop 1 and I go to the right 1, 2, 3, I'm back on the line, okay? So you can see that's where the slope is. The y-intercept is unfortunately not an integer value, but you could check other points on the line to make sure you got it correct. Now, how can we find this point right here, the point of intersection? Remember, this is nothing more than just solving a system of linear equations, right? We're trying to find the point that basically satisfies both. So if we go back and we think about this, we have each one solved for y. So what I could do is I could actually set this guy right here equal to this guy right here. Why? I'm doing nothing more than just the substitution method. If y is equal to this, well then I can just plug this in for y right there, right? That's all I'm really doing. So I could say 3x plus 4 is equal to negative 1/3 times x plus 14/3, okay? And then I just want to solve for x, figure out what that's going to be. So let's multiply everything by 3, get rid of the denominators. This is 9x plus 12 is equal to, we'll put negative x, and then plus 14, okay? So now it's going to make it a little bit easier. Let's go ahead and add x to both sides of the equation. Let's subtract 12 from both sides of the equation. And so this is going to cancel, and this is going to cancel. So you have 10x is equal to, we'll say 2. Divide both sides by 10, and you'll get x is equal to 1/5. Okay? So the x value that we're looking for is 1/5. So let me put that in here. So the x value, x is equal to 1/5. So the y value is equal to what? Remember, if the x value is 1/5, it's 1/5 here, and it's also 1/5 here. So I can plug it into either original equation and solve for the corresponding y value. Again, this is going to be the point that solves both, okay? So we'll go ahead and say y is equal to, I'll say 3 times 1/5, and then plus 4, okay? So 3 times 1/5 is going to be 3/5. So let's say this is 3/5. I need a common denominator, so let's write this as 20/5, right? 20 divided by 5 is 4. So basically this is going to be 23/5. So y is 23/5. Okay, so not the nicest point that you could come up with, but still you can work with it. So the point of intersection for these two lines is going to be 1/5, 23/5. And if you go back, that looks about right. So we can say this guy right here would be 1/5. Okay, that's the x coordinate, comma 23/5, that is your y coordinate. Okay, so now I just need to find the distance between this point and this point here. Okay, that's all I want to do, and that's just the regular distance formula. So the distance is equal to, remember, the square root of, you would take the difference in x values. So I can go ahead and say this is, let's say, my second point right here. So I'll say this is my x sub 2 comma y sub 2. And remember, we're working with this point right here because this is the point we're trying to find the distance to. So we'll say this is x sub 1. We'll say this is y sub 1. Okay, so you want your x sub 2 minus your x sub 1. So 1/5 minus your 5. This is going to be squared, plus you're going to take your 23/5, so your 23/5, and this is going to be minus 3, and then this is going to be squared. Okay, so I know a lot of you don't like working with fractions, but it's really not that bad. So the distance is equal to the square root of. So I need a common denominator here. Let's write this as 25/5, and let's go ahead and write this as 15 over 5. Okay, So 1 minus 25 is going to be negative 24. So this is negative 24 fifths. This is going to be squared. Then plus 23 minus 15 is going to give me 8. So this would be 8 fifths, and this is going to be squared. Okay? So the distance is equal to the square root of, if you square 5, obviously you get 25. If you square negative 24, you're going to get positive 576. So then plus, this would obviously be 64 over 25. If you want to add these two together, because you do have a common denominator, you would have 576 plus 64, which is 640. So the distance is equal to the square root of 640 over 25. So just simplifying this, the distance is equal to the square root of 640 divided by 5 is 128. And then 25 divided by 5 is 5. Okay, so this is a little bit more manageable, something you could probably do without your calculator. So you know 128 is 64 times 2, and 64 is a perfect square, right? It's 8 times 8. So I could say that the distance is equal to, I'll go ahead and say, first let me break this up and say this is the square root of 128 over the square root of 5. Okay, so we have this established. Then let me write up here, let me make a little border. I'll actually do this in a different color. I'll say that the distance is equal to, this is going to be 8 times the square root of 2, and then over, you have the square root of 5. And then I'm going to rationalize the denominator, okay, just like we did before. And basically, I'm going to end up with a distance that is 8 times the square root of 10 over 5. Okay, so the same answer we got before. Obviously, it took way longer, but hopefully this gives you a little bit of insight into where that formula came from. All right, let's take a look at one more example. We'll do this the short way using the formula. Obviously, you can pause the video and try this the long way. That's up to you. So we have 2x minus y equals negative 1. So I want to write this as 2x minus y plus 1 equals 0. So very important to do this. This is your A. This is your B. It's going to be negative 1 again. And then this is your C. Okay? Then your point here, 4 comma 1, this is your x sub 1. This is your y sub 1. Okay? So the distance is equal to, go ahead and plug in. So you have the absolute value of, remember it's A, which is 2, times x sub 1, which is 4. Then plus, you have b, which is negative 1. Then times your y sub 1, which is 1. Then plus, you're going to have your c, which is 1. Okay? That's your numerator. Then over the denominator, which is the square root of, you have your a, which is 2, being squared. So let's just go ahead and write that as 4. Then plus, you have your b, which is negative 1, being squared. Let's write that as 1. Okay? So let's come down here, and I'll go ahead and say the distance is equal to 2 times 4 is 8. Then you would basically have minus 1 plus 1. So let's just go ahead and say this is the absolute value of 8, which is 8. And then over the square root of 5, you can rationalize the denominator there. And we'll go ahead and say this is going to be 8 times the square root of 5 over 5 as our answer.